Welcome to Simplilearn's YouTube channel. Modern organizations generate massive volumes of data from applications, transactions, sensors, websites, connected devices, and business systems. And handling this data requires more than traditional tools. Professionals need scalable technologies that can store, process, analyze, and interpret large data sets efficiently. And that is where big data, Apache Spark, and R programming come together. Big data technologies help organizations manage data sets that are too large, fast, or complex for traditional systems. Hadoop provides a distributed framework for storing and processing large amounts of data, while technologies such as HDFS, MapReduce, Yarn, and Sqoop help manage different parts of big data ecosystem. Apache Spark takes distributed data further by providing a fast and flexible platform for large-scale analytics. It supports batch processing, streaming data, SQL workloads, machine learning, and Python-based analytics through PySpark. R programming adds another important analytic layer. It provides powerful capabilities for working with structured data, manipulating datasets, performing statistical analysis, creating visualizations, and analyzing time series information. Together, these technologies allow professionals to move from storing and processing massive datasets to analyzing them and extracting meaningful insights. Having said that, let's have a look at the agenda for this course. We will be starting off with evolution of big data fundamentals, the 5 V's, and the big data challenges. Hadoop fundamentals, Hadoop installation, and the Hadoop ecosystem. Hadoop distributed file system, HDFS architecture, and distributed storage. MapReduce, parallel processing, workflow architecture, and Hadoop 10. Yarn, resource management, node manager, and Hadoop processing architecture. Sqoop, data transfer, Sqoop features, and architecture. Introduction to Apache Spark, Spark installation, and Spark architecture. Spark streaming, Spark SQL, Spark MLlib, PySpark, and Spark case studies. Introduction to R programming, variables, data types, and logical operators. Vectors, lists, matrices, data frames, and flow control in R. Hope I made myself clear with the agenda. That being said, if these are the types of videos that you would like to watch, then hit that subscribe button along with the bell icon to get notified whenever we upload a new video. Also, just that you know, if you want to upskill yourself mastering data science and data analytics skill and land your dream job or grow in your career, then you must explore Simplilearn's cohort of various data science and data analytics programs. Simplilearn offers a variety of master certifications and postgraduate programs in collaboration with some of the world's leading universities. Through our courses, you will gain the knowledge and work-ready expertise in skills like Python, Tableau, Power BI, generative AI, and over a dozen others. And that's not all. You get the opportunity to work on multiple projects led by industry experts working in top-tier data and product companies. After completing all of these courses, thousands of learners have transitioned into data science or data analytics role as a fresher or moved onto a higher-paying job and profile. Now, if you're passionate about making your career in this field, then make sure to check out the link in the pinned comment and the description box to find a data science and data analytics program that fits your experience and areas of interest. Now over to our training experts.
Now, when we talk about evolution of big data, we have known that data has evolved in last 5 years like never before. Now, in fact, before going to big data or before understanding these solutions and the need and why there is a rush towards big data technology and solution, I would like to ask a question. Take a couple of minutes and think, why are organizations interested in big data? Why is there sudden rush in industry where everyone would want to ramp up their current infrastructure or would want to be working on technologies which allow them to use this big data? Think about it. What is happening and why are organizations interested in this? And if you think on this, you will start thinking about what organizations have been doing in past, what organizations have not done, and why are organizations interested in big data. Now, before we learn on big data, we can always look into internet and check for use cases where organizations have failed to use legacy systems or relational databases to work on their data requirements. Now, over past 5 years or in recent decade, what has happened is organizations have started understanding the value of data, and they have decided not to ignore any data as being uneconomical. Now, we can talk about different platforms through which data is generated. Take an example of social media like Twitter, Facebook, Instagram, WhatsApp, YouTube. You have e-commerce and various portals, say eBay, Amazon, Flipkart, Alibaba.com. And then you have various tech giants such as Google, Oracle, SAP, Amazon, Microsoft, and so on. So lots of data is getting generated every day in every business sector. The point here is that organizations have slowly started realizing that they would be interested in working on all the data. Now, the question which I asked was, why are organizations interested in big data? And some of you might have already answered or thought about that organizations are interested in doing precise analysis, or they want to work on different formats of data, such as structured, unstructured, semi-structured data. Organizations are interested in gaining insights or finding the hidden treasure in the so-called big data. And this is the main reason where organizations are interested in big data. Now, there are various use cases. We can compare that organizations from past 50 or more than 50 years have been handling huge amount of data. They have been working on huge volume of data. But the question here is, have they worked on all the data, or have they worked on some portion of it? What have they used to store this data? And if they have used something to store this data, what is happening? What is changing now? When we talk about the businesses, we cannot avoid talking about the dynamism involved. Now, any organization would want to have a solution which allows them to store data and store huge amount of data, capture it, process it, analyze it, and also look into the data to give more value to the data. Organizations have then been looking for solutions. Now let's look at some facts that can convince you, or that would convince you, that data is exploding and needs your attention, right? 55 billion messages and 4.5 billion photos are sent each day on WhatsApp. 300 hours of video are uploaded every minute on YouTube. Did you guys know that YouTube is the second largest search engine after Google? Every minute, users send 31.25 million messages and watch 2.77 million videos on Facebook. Walmart handles more than 1 million customer transactions every hour. Google, 40,000 search queries are performed on Google per second. That is 3.46 million searches a day. In fact, you could also say that a lot of times people, when they are loading up the Google page, is basically just to check their internet connection. However, that is also generating data. IDC reports that by 2025, real-time data will be more than a quarter of all the data. And by 2025, the volume of digital data will increase to 163 zettabytes. That is, we are not even talking about gigabytes or terabytes anymore. We are talking about petabytes, exabytes, and zettabytes. And zettabytes means 10 to the power 21 bytes. So this is how data has evolved. Now, you can talk about different companies which would want to use their data to take business decisions. They would want to collect the data, store it, and analyze it. And that's how they would be interested in drawing insights for the business. Now, this is just a simple example about Facebook and what it does to work on the data. Now, before we go to Facebook, you could always check in Google by just typing in companies using big data. And if we say companies using big data, we should be able to find a list of different companies which are using big data for different use cases. There are various sources from where you can find. We could also search for solution, that is Hadoop, which we'll discuss later, but you could always say companies using Hadoop, and that should take you to the wiki page, which will basically help you know what are the different companies which are using this so-called solution called Hadoop. Okay, now coming back to what we were discussing about, so organizations are interested in big data, as we discussed, in gaining insights. They would want to use the data to find hidden information which probably they ignored earlier. Now take an example of RDBMS. What is biggest drawback in using an RDBMS? Now you might think that RDBMS is known for stability and consistency, and organizations would be interested in storing their data in Oracle or DB2 or MySQL or Microsoft SQL Server, and they have been doing that for many years now. So what has changed now? Now, when we talk about RDBMS, the first question which I would ask is, do we have access to 100% of data being online in RDBMS? The answer is no. We would only have 10 or 20 or 30% of data online, and rest of the data would be archived. which means that if an organization is interested in working on all the data, they would have to move the data from the archived storage to the processing layer, and that would involve bandwidth consumption. Now, this is one of the biggest drawbacks of RDBMS. You do not have access to 100% of data online. In many of the cases, organizations started realizing that the data which they were ignoring as being uneconomical had hidden value which they had never exploited. I had read a presentation somewhere which said, torture the data and it will confess to anything. Now that's the value of data which organizations have realized in recent past. Take an example of Facebook. Now this shows what Facebook does with its big data. And we'll come to what is big data, but let's understand a use case. Now, Facebook collects huge volumes of user data, whether that is SMS, whether that is likes, whether that is advertisements, whether that is features which people are liking, or photographs, or even user profiles. Now, by collecting this data and providing a portal which people can use to connect, Facebook is also accumulating huge volume of data, and that's way beyond petabytes. They would also be interested in analyzing this data, and one of the reasons would be they would want to personalize the experience. Take an example of personalized news feed. Depending on a user behavior, depending on what a user likes, what a user would want to know about, they can recommend a personalized news feed to every particular user. That's just one example of what Facebook does with its data. Take an example of photo tag suggestions. Now, when you log into Facebook account, you could also get suggestions on different friends whom you would like to connect to, or you would want to tag so that they could be known by others. Some more examples which show how Facebook uses its data are as follows. So the flashback, collection of photos and posts that receive the most comments and likes. Okay, there was something called as I voted that was used for 2016 elections with reminders and directions to tell users their time and place of polling. Also, something called as safety checks. In incidents such as earthquake, hurricane, or mass shooting, Facebook gives you safety checks. Now, these are some examples where Facebook is using big data. And that brings us to the question, what is big data? This was just an example where we discussed about one company which is making use of that data which has been accumulated. And it's not only for companies which are social media oriented like Facebook, where data is important. Take an example of IBM, take an example of JP Morgan Chase, take an example of GE, or any other organization which is collecting huge amount of data. They would all want to gather insights, they would want to analyze the data, they would want to be more precise in building their services or solutions which can take care of their customers. So what is big data? Big data is basically a term. It is used to describe the data that is too large and complex to store in traditional databases. And as I gave an example, it's not just about storing the data. It is also about what you can do with the data. It also means that if there is a lot of dynamism involved, can you change the underlying storage and handle any kind of data that comes in? Now, before we get into that, let's just understand what is big data. So big data is basically a term which has been given to categorize the data if it has different characteristics. Organizations would want to have the big data stored, processed, and then analyzed to get whatever useful information they can get from this data. Now, there are 5 V's of big data: volume, velocity, variety, value, veracity. Although these are 5 V's, but then there are other V's which also categorize the data as big data, such as volatility, validity, viscosity, virality of data. Okay, so these are 5 V's of big data, and if the data has one or all of these characteristics, then it can be considered as big data, including the other V's which I just mentioned. So volume basically means incredible amount of data, huge volumes of data. data generated every second. Now that could be used for batch processing, that could be used for real-time stream processing. Okay, you might have data being generated from different kind of devices like your cell phones, your social media websites, online transactions, wearable devices, servers, and these days with IoT, we are also talking about data getting generated via Internet of Things. That is, you could have different devices which could be communicating to each other. You could be getting data from radars or lidars or even camera sensors. So there is a huge volume of data which is getting generated. And if we are talking about data which has huge volume, which is getting generated constantly or has been accumulated over a period of time, we would say that is big data. Velocity. Now this is one more important aspect of big data. Speed with which the data is getting generated. Think about stock markets, think about social media websites, think about online surveys or marketing campaigns or airline industry. So if the data is getting generated with a lot of speed, where it becomes difficult to capture, collect, process, cure, mine, or analyze the data, then we are certainly talking about big data. The next aspect of big data is variety. Now, this is where we talk about structured data, semi-structured data, or unstructured data. And here I would like to ask a question. What is the difference? When do you call the data as structured, semi-structured, or unstructured? Now let's look at an example before we theoretically discuss about this. I always would like to use some examples. Let's look at a log file and let's see what is it. So if I look at this log file and if I would say what kind of data is this, which is the highlighted one, the answer would be it is structured data. It has specific delimiters such as space. It has data which is separated by space. And if I had 100 or 1,000 or million rows which had similar kind of data, I could certainly store that in a table. I could have a predefined schema to store this data. So I would call the one which is highlighted as structured. But if I look at this portion where I would look at a combination of this kind of data where some data has a pattern and some data doesn't. Now this is an example of semi-structured data. So if I would have a predefined structure to store this data, probably the pattern of data would break the structure. And if I look at all the data, then I would certainly call it unstructured data because there is no clear schema which can define this data. Now this is what I mean by variety of data. That is structured data which basically has a schema or has a format which could be easily understood. You have semi-structured, which could be like in XML or JSON or even your Excel sheets, where you could have some data which is structured and the other is unstructured. And when we talk about unstructured, we are talking about absence of schema. It does not have a format, it does not have a schema, and it is hard to analyze, which brings its own challenges. The next aspect is value. Now, value refers to the ability to turn your data useful for business. You would have a lot of data which is being collected, as we mentioned in previous slides, right? There would be a lot of data wrangling or data pre-processing or cleaning up of data happening. And then finally, you would want to draw value from that data. But from all the data collected, what percentage of data gives us value? And if all my data can give me value, then why wouldn't I use it? This is an aspect of big data, right? Veracity. Now this means the quality of data. Billions of dollars are lost every year by organizations because the data which was collected was not of good quality, or probably they collected a lot of data and then it was erroneous. Take an example of autonomous driving projects which are happening in Europe or US, where there are car fleets which are on the road collecting data via radar sensors and camera sensors. And when this data has to be processed to train algorithms, it is realized that sometimes the data which was collected was missing in some values, might be was not appropriate, or had a lot of errors. And all this process of collecting the data becomes a repetitive task because the quality of data was not good. This is just one example. We can take example from healthcare industry or stock markets or financial institutions and so on. So extracting loads of data is not useful if the data is messy or poor in quality. And that basically means that veracity is a very important V of big data. Now, apart from veracity, volume, variety, velocity, and value, we have the other V's such as viscosity, how dense the data is. Validity, is the data still valid? Volatility, is my data volatile? Or virality, is the data viral? Now, all of these different V's categorize the data as big data. We would like to talk on a big data case study, and we have taken an example of Google, which obviously is one of the companies which is churning and working on huge amount of data. Now, it's actually said that if you compare one grain of sand with one byte of data, then Google is processing, or Google is handling whole world's sand every week. That is the kind of data which Google is processing. Now, in early 2000 and since then, when the number of internet users started growing, Google also faced a lot of problems in storing, increasing user data, and using the traditional servers to manage that. Now, that was a challenge which Google started facing. Could they use traditional data server to store the data? Well, yes, they could, right? Storage devices have been getting cheaper day by day. But then, how much time does it take to retrieve that data? What is the seek time? What is the time taken to read and process that data? Thousands of search queries were raised per second, no doubt. Now we could say millions and billions of queries are raised per second. Every query read 100 MBs of data and consumed tens of billions of CPU cycles based on these queries. So the requirement was that they wanted to have a large, distributed, highly fault tolerant file system. Large to store, to capture, process huge amount of data. Distributed because they could not rely just on one server. Even if that had multiple disks stacked up, that was not an efficient choice. What would happen if this particular machine failed? What would happen if the whole server was down? So they needed a distributed storage and a distributed computing environment. They needed something which can be highly fault tolerant, right? So this was the requirement which Google had, and the solution which came out as a result was GFS, Google File System. Now let's look at how GFS works. So normally in any particular Linux system or Linux server, you would have a file system. You would have set of processes, you would have set of files and directories which could store the data. GFS was different. So to facilitate GFS, which could store huge amount of data, there was an architecture which had one master and multiple chunk servers, or you can say slave servers or slave machines. Master machine was to contain metadata, was to contain data about data. When we say metadata, we are talking about information about data. And then you have the chunk servers or the slave machines, which could be storing data in a distributed fashion. Now, any client or an API or an application which would want to read the data would first contact the master server. It would contact the machine where the master process was running, and client would place a request of reading the data or showing an interest of reading the data. Internally, what it is doing is it is requesting for metadata. Your API or an application would want to know from where it can read the data. Master server, which has metadata, whether that is in RAM or disk, we can discuss that later. But then master server would have the metadata, and it would know which are the chunk servers or the slave machines where the data was stored in a distributed fashion. Master would respond back with the metadata information to the client, and then client could use that information to read or write to these slave machines where actually the data was stored. Now this is what the process or set of processes work together to make GFS. So when you say a chunk server, we would basically have the files getting divided into fixed size chunks. Now, how would they get divided? So there would be some kind of chunk size or a block size which would determine that. If the file is bigger than the pre-decided chunk size, then it would be split into smaller chunks and be distributed across the chunk servers or the slave machines. If the file was smaller, then it would still use one chunk or a block to get stored on the underlying slave machines. So these chunk servers or slave machines are the ones which actually store the data on local disks as your Linux files. Client, which is interacting with master for metadata and then interacting with chunk servers for read-write operations, would be the one which would be externally connecting to the cluster. So this is how it would look. So you have a master which would obviously be receiving some kind of heartbeats from the chunk servers to know their status and receive information in the form of packets which would let the master know which machines were available for storage, which machines already had data, and master would build up the metadata within itself. The files would be broken down into chunks. For example, we can look at file 1. It is broken down into chunk 1 and chunk 2, and file 2 has one chunk which is one portion of it, and then you have file 2 residing on some other chunk server, which also lets us know that there is some kind of auto replication for this file system, right? And the data which is getting stored in the chunk could have a data of 64 MB. Now that chunk size could be changed based on the data size, but Google File System had the basic size of the chunk as 64 MB. Each chunk would be replicated on multiple servers. The default replication was 3, and that could again be increased or decreased as per requirement. This would also mean that if a particular slave machine or a chunk server would die or would get killed or would crash, there would never be any data loss, because a replica of data residing on the failed machine would still be available on some other slave server, chunk server, or slave machine. Now this helped Google to store and process huge volumes of data in a distributed manner and thus have a fault tolerant, distributed, scalable storage which could allow them to store a huge amount of data. Now that was just one example which actually led to the solution which today we call as Hadoop. Now when we talk about big data, here I would like to ask you some questions, that if we were talking about the RDBMS case, take an example of something like NASA, which was working on a project called SETI, Search of Extraterrestrial Intelligence. Now this was a project where they were looking for a solution to take care of their problem. The problem was that they would roughly send some waves in space, capture those waves back, and then analyze this data to find if there was any extraterrestrial object in space. Now they had two options for it. They could either have a huge server built which could take care of storing the data and processing it, or they could go for volunteer computing. Now volunteer computing basically means that you could have a lot of people volunteering and being part of this project, and what they would in turn do is they would be donating their RAM and storage from their machines when they are not using it. How would that happen? Basically download some kind of patch on their machine which would run as a screensaver, and if the user is not using his machine, some portion of data could be transferred to these machines for intermittent storage and processing using RAM. Now this sounds very interesting and this sounds very easy. However, it would have its own challenges, right? Think about security, think about integrity, but those problems are not bigger as much as is the requirement of bandwidth. And this is the same thing which happens in RDBMS. If you would have to move data from archived solution to the processing layer, that would consume huge amount of bandwidth. Big data brings its own challenges. Huge amount of data is getting generated every day. Now the biggest challenge is storing this huge volume of data, and especially when this data is getting generated with a lot of variety, when it can have different kind of formats, where it could be viral, it could be having a lot of value, and nobody has looked into the veracity of data. But the primary problem would be handling this huge volume of data. Variety of the data would bring in challenges of storing it in legacy systems if processing of the data was required. Now here again I would suggest you need to think, what is the difference between reading a data and processing a data? So reading might just mean bringing in the data from disk and doing some IO operations, and processing would mean reading the data, probably doing some transformations on it, extracting some useful information from it, and then storing it in the same format or probably in a different format. So processing this massive volume of data is the second challenge. Organizations don't just store their big data. They would eventually want to use it, to process it, to gather some insights. Now, processing and extracting insights from big data would take huge amount of time unless and until there was an efficient solution to handle and process this big data. Securing the data, that's again a concern for organizations, right? Encryption of big data is difficult to perform. If you would think about different compression mechanisms, then that would also mean decompressing of data, which would also mean that you could take a hit on the CPU cycles or on disk usage. Providing user authentication for every team member, now that could also be dangerous. So that led to Hadoop as a solution. So big data brings its own challenges. Big data brings its own benefits. And here we have a solution, which is Hadoop. Now what is Hadoop? It's an open source framework for storing data and running applications on clusters of commodity hardware. Hadoop is an open source framework. And before we discuss on two main components of Hadoop, it would be good to look into the link which I was suggesting earlier, that is companies using Hadoop. And any person who would be interested in learning big data should start somewhere here, where you could list down different companies, what kind of setup they have, why are they having Hadoop, what kind of processing they are doing, and how are they using these so-called Hadoop clusters to process and in fact store, capture, and process huge amount of data. Another link which I would suggest is looking at different distributions of Hadoop. Any person who is interested in learning in big data should know about different distributions of Hadoop. Now in Linux, we have different distributions like Ubuntu, CentOS, Red Hat, SUSE, Debian. In the same way, you have different distributions of Hadoop, which we can look on the wiki page. And this is the link which talks about products that include Apache Hadoop or derivative works and commercial support, which basically means that Apache Hadoop, the sole products that can be called a release of Apache Hadoop come from apache.org. That's an open source community. And then you have various vendor specific distributions like Amazon Web Services, you have Cloudera, you have Hortonworks, you have IBM's Big Insight, you have MapR. All these are different distributions of Hadoop. So basically all of these vendor specific distributions are depending or using on core Apache Hadoop. In brief, we can say that these are the vendors which take up the Apache Hadoop, package it within a cluster management solution so that users who intend to use Apache Hadoop would not have difficulties of setting up a cluster, setting up a framework. They could just use a vendor specific distribution with its cluster installation solutions, cluster management solution, and easily plan, deploy, install, and manage a cluster. Here is a quick demo on setting up Cloudera Quick Start VM in case you are interested in working on a standalone cluster. You can download the Cloudera Quick Start VM. So you can just type in download Cloudera Quick Start VM and you can search for package. Now this can be used to set up a quick start VM, which would be a single node Cloudera based cluster. So you can click on this link and then basically based on the platform which you would be choosing to install, such as using a VM box or which version of Cloudera you would install. So here I can select a platform, so I can choose VirtualBox and then you can click on get it now. So give your details and basically then it should allow you to download the quick start VM, which would look something like this. And once you have the zip file which is downloaded, you can unzip it, which can then be used to set up a single node Cloudera cluster. So once you have downloaded the zip file, that would look something like this. So you would have a quick start VirtualBox and then a VirtualBox disk Now this can be used to set up a cluster. Ignore these files which are related to Amazon machines, and you don't need to have that. So you would just have this, and this can be used to set up a Cloudera cluster. So for this to be set up, you can click on File, Import Appliance, and here you can choose your Quick Start VM by looking into Downloads, Quick Start VM, select this and click on Open. Now you can click on Next, and that shows you the specifications of CPU, RAM, which we can then change later, and click on Import. This will start importing virtual disk image .vmdk file into your VM box. Once this is done, we will have to change the specifications of our machines to use 2 CPU cores minimum and give a little more RAM, because Cloudera Quick Start VM is very CPU intensive and it needs good amount of RAM. So to survive, I will give 2 CPU cores and 5 GB RAM, and that should be enough for us to bring up a Quick Start VM, which gives us a Cloudera distribution of Hadoop in a single node cluster setup, which can be used for working, learning about different distributions in Cloudera cluster, working with HDFS and other Hadoop ecosystem components. Let's just wait for this importing to finish, and then we will go ahead and set up a Quick Start VM for our practice. Here the importing of appliance is done, and we see Cloudera Quick Start machine is added to my list of machines. I can click on this and click on Settings. As mentioned, I would like to give it more RAM and more CPU cores. So click on System, and here let's increase the RAM to at least 5, and click on Processor, and let's give it 2 CPU cores, which would at least be better than using 1 CPU core. Network, it goes for NAT, and that's fine. Click on OK, and we would want to start this machine so that it uses 2 CPU cores, 5 GB RAM, and it should bring up my Cloudera Quick Start VM. Now let's go ahead and start this machine, which has our Quick Start VM. It might take initially some time to start up, because internally there will be various Cloudera services which will be starting up, and those services need to be up for our Cloudera Quick Start VM to be accessible. So unlike your Apache Hadoop cluster, where we start our cluster and we will be starting all our processes, in case of Cloudera, it is your Cloudera SCM server and agents which take care of starting up of your services and starting up of your different roles for those services. I explained in my previous session that for a Cloudera cluster, it would be these services. Let me just show you that. So in case of Apache cluster, we start our services, that is, we start our cluster by running script, and then basically those scripts will individually start the different processes on different nodes. In case of Cloudera, we would always have a Cloudera SCM server which would be running on one machine, and then including that machine, we would have Cloudera SCM agents which would be running on multiple machines. Similarly, if we had a Hortonworks cluster, we would have Ambari server starting up on the first machine, and then Ambari agents running on other machines. So your server component knows what are the services which are set up, what are their configurations, and agents running on every node are responsible to send heartbeats to the server, receive instructions, and then take care of starting and stopping up of individual roles on different machines. In case of our single node cluster setup in Quick Start VM, we would just have one SCM server and one SCM agent which will start on the machine, which will then take care of all the roles which need to be started for your different services. So we will just wait for our machine to come up and basically have Cloudera SCM server and agent running. And once we have that, we need to follow few steps so that we can have the Cloudera admin console accessible, which allows you to browse the cluster, look at different services, look at the roles for different services, and also work with your cluster either using command line or using the web interface, that is Hive. Now that my machine has come up and it already is connected to the internet, which we can see here, we need to do certain things so that we can have our admin console accessible. At this point of time, you can click on terminal and check if you have access to the cluster. So here type in host name and that shows you your host name, which is quickstart.cloudera. We can also type in HDFS command to see if we have access and if my cluster is working. These commands are same as you would give them in a Apache Hadoop cluster or in any other distribution of Hadoop. Sometimes when your cluster is up and you have access to the terminal, it might take few seconds or few minutes before there is a connection established between Cloudera SCM server and Cloudera SCM agent running in the background, which takes care of your cluster. I have given HDFS DFS list command, which basically should show me what by default exists on my HDFS. Let's just give it a couple of seconds before it shows us the output. We can also check by giving a service Cloudera SCM server status, and here it tells me that if you would want to use Cloudera Express free, run this command. It needs 8 GB of RAM and at least 2 virtual CPU cores. And it also mentions it may take several minutes before Cloudera Manager has started. I can log in as root here and then give the command service Cloudera SCM server status. Remember, the password for root is Cloudera. So it basically says that if you would want to check these settings, it is good to have Express Edition running. So we can close this. My HDFS access is working fine. Let's close the terminal, and here we have launch Cloudera Express. Click on this and that will give you that you need to give a command, which is force. Let's copy this command. Let's open a different terminal and let's give this command like this, which will then go ahead and shut down your Cloudera based services, and then it will restart it, only after which you will be able to access your admin console. So let's just give it a couple of minutes before it does this, and then we will have access to our admin console. Here if you see, it is starting the Cloudera Manager server again. It is waiting for Cloudera Manager API, then starting the Cloudera Manager agents, and then configuring the deployment as per the new settings which we have given as to use the Express edition of Cloudera. Once all this is done, it will say the cluster has been restarted and the admin console can be accessed by ID and password as Cloudera. We'll give it a couple of more minutes, and once this is done, we are ready to use our admin console. Now that deployment has been configured, client configurations have also been deployed, and it has restarted the Cloudera management service, it gives you an access to quick start admin console using username and password as Cloudera. Let's try accessing it. So we can open up the browser here and let's change this to 7180. That's the default port, and that shows the admin console which is coming up. Now here we can log in as Cloudera, and then let's click on login. Now, as I said, Cloudera is very CPU intensive and memory intensive, so it would slow down since we have not given enough GB RAM to our Cloudera cluster, and thus it will be advisable to stop or even remove the services which we don't need. Now, as of now, if we look at the services, all of them look in a stop status, and that's good in one way because we can then go ahead and remove the services which we will not use in the beginning, and later we can anytime add services to the cluster. So for example, I can click on key value store here, and then I can scroll down where it says delete to remove this service from the admin console. Now anytime you are removing a particular service, it will only remove the service from the management by Cloudera Manager. All the role groups under this service will be removed from host templates. So we can click on delete. Now if this service was depending on some other service, it would have prompted me with a message that remove the relevant services on which this particular service depends. If the service was already running, then it would have given me a message that the service has to be stopped before it can be deleted from the Cloudera admin console. Now this is my admin console, which allows you to click on services, look at the different roles and processes which are running for this service, we anyways have access to our Cloudera cluster from the terminal using our regular HDFS or yarn or MapRed commands. Now I removed a service. I will also remove Solar, which we will not be using for the beginning, but then it depends on your choice. So we can here scroll down to delete it, and that says that before deleting the Solar service, you must remove the dependencies on this service from the configuration of following services, that is Hue. Now Hue is a web interface which allows you to work with your HDFS, and that is depending on this. So click on configure service dependency, and here we can make sure that our Hue service does not depend on a particular service we are removing, so that then we can have a clean removal of the service. So I'll click on none and I will say save changes. Once this is done, then we can go ahead and try removing the Solar service from our admin console, which will reduce some load on my management console, which will also allow me to work faster on my cluster. Now here we have removed the dependency of Hue on Solar, so we can click on this and then we can delete it. Remember, I'm only doing this so that my cluster becomes a little lighter and I can work on my focus services. At any point of time, if you want to add more services to your cluster, you can anytime do that. You can fix different configuration issues like what we see here with different warning messages. And here we have these services which are already existing. Now if we don't need any of the service, I can click on the drop down and click on delete. Again, this says that Sqoop 2 also has relevance to Hue. So Hue as a web interface also depends on Sqoop 2. As of now, we'll make it none. At any point of time later, you can add the services by clicking the add service option. Now this is a cluster to which you have admin access, and this is a quick start VM which gives you a single node Cloudera cluster which you can use for learning and practicing. So here we'll click on Sqoop 2 and then we will say delete, as we have configured the dependency now, and we will remove Sqoop 2 also from the list of services which your admin console is managing, right? So once this is done, we have removed 3 services which we did not need. We can even remove Sqoop as a client, and if we need, we can add that later. Now there are various other alerts which your Cloudera admin console shows, and we can always fix them by clicking on the health issues or configuration issues. We can click here and see what is the health issue it is pointing to, if that is a critical one or if that can be ignored. So it says there is an issue with a clock offset, which basically relates to an NTP service, network time protocol, which makes sure that one or multiple machines are in the same time zone and are in sync. So for now, we can click on suppress and we can just say suppress for all hosts, and we can say look into it later and confirm. So now we will not have that health issue reported, that probably the NTP service and the machines might not be in sync. Now that does not have an impact for our use case as of now, but if we have a Kerberos kind of setup which is for security, then basically this offset and time zone becomes important. So we can ignore this message and we are still good to use the cluster. We also have other configuration issues, and you can click on this, which might talk about the heap size or the RAM which is available for machines. It talks about Zookeeper should be in odd numbers. Hue does not have a load balancer. HDFS only has one data node. But all of these issues are not to be worried upon because this is a single node cluster setup. So if you want to avoid all of these warnings, you can always click on suppress and you can avoid and let your cluster be in all green status. But that's nothing to worry. So we can click on cluster and basically we can look at the services. So we have removed some services which we don't intend to use now. I have also suppressed a offset warning which is not very critical for my use case, and basically I'm good to start the cluster. At any point of time, as I said, if you would want to add services, this is the actions button which you can use to add service. So we will just say restart my cluster, which will restart all the services one by one, starting from Zookeeper as the first service to come up. We can always click on this arrow mark and see what is happening in the services, what services are coming up and in which order. If you have any issues, you can always click on the link next to it, which will take you to the logs, and we can click on close to let it happen in the background. So this will basically let my services restart one by one, and my cluster will then become completely accessible either using Hive as a web interface or quick start terminal, which allows you to give your commands. Now while my machines are coming up, you can click on hosts and you can have a look at all the hosts we have. As of now only one, which will also tell you how many roles or processes are running on this machine. So that is 25 roles. It tells you what is the disk usage. It tells you what is the physical memory being used. And using this host tab, we can add new hosts to the cluster. We can check the configuration. We can check all the hosts. In diagnostics, you can look at the logs, which will give you access to all the logs. You can even select the sources from which you would want to have the logs, or you can give the host name. You can click on search. You can build your own charts. You can also do the admin stuff by adding different users or enabling security using the administration tab. So since we have clicked on restart of a cluster, we will slowly start seeing all the services one by one coming up, starting with Zookeeper to begin with. And once we have our cluster up and running, whether that is showing all services in green or in a different status, we still should be able to access the service. Now, as we saw in Apache Hadoop cluster, even here we can click on HDFS and we can access the web UI once our HDFS service is up by clicking on quick links. So the service is not yet up. Once it is up, we should be able to see the web UI link, which will allow you to check things from HDFS web interface. Similarly, Yarn as a service also has a web interface. So as soon as the service comes up, under your quick links, we will have access to the Yarn UI. And similarly, once the service comes up, we will have access to Hive, which will give you the web interface, which allows you to work with your HDFS, which allows you to work with your different other components within the cluster without even using the command line tools or command line options. So we will have to give it some time while the Cloudera SCM agent on every machine will be able to restart the roles which are responsible for your cluster to come up. We can always click here, which tells that there are some running commands in the background which are trying to start my cluster. We can go to the terminal and we can switch as HDFS user. Remember, HDFS user is the admin user and it does not have a password unless you have set one. So you can just log in as HDFS, which might ask you for a password initially, which we do not have. So the best way to do this is by logging in as root, where the password is Cloudera, and then you can log in as HDFS, so that then onwards you can give your HDFS commands to work with your file system. Now, since my services are coming up right now, when I try to give a HDFS DFS command, it might not work, or it might also say that it is trying to connect to the name node, which is not up yet. So we will have to give it some time, and only once the name node is up, we will be able to access our HDFS using commands. So this is how you can quickly set up your quick start, and then you can be working using the command line options from the terminal, like what you would do in an Apache Hadoop cluster. You could use the web interfaces which allow you to work with your cluster. Now this usually takes more time, so you will have to give it some time before your services are up and running. And for any reason, if you have issues, it might require you to restart your cluster several times in the beginning before it gets accustomed to the settings what you have given and it starts up the services. At any point of time, if you have any error message, then you can always go back and look in logs and see what is happening and try starting your cluster. So this is how we set up a quick start VM, and you can be using this to work with your Cloudera cluster. And welcome to the tutorial where we will learn today on setting up a Apache Hadoop cluster. Although there are various distributions of Hadoop, as we have already discussed, and you could set up a Apache Hadoop cluster, which is the core distribution. You could be setting up a Cloudera distribution of Hadoop or even a Hortonworks. However, for Cloudera, you would need machines which are really powerful, at least machines which have 16 GB of RAM and in which you can set up multiple virtual machines, each virtual machine of at least 4 to 5 GB. Same thing applies for Hortonworks, or you could always download and set up a Cloudera Quick Start VM or a Hortonworks sandbox. In this session, we will learn how to set up a Apache Hadoop cluster, which is the core distribution. And if one has learned how to set up Apache Hadoop cluster, then they would understand the internals of setting up a cluster, different configuration properties which are needed for your cluster setup. We can say that these are the vendors which take up the Apache Hadoop, package it within a cluster management solution so that users who intend to use Apache Hadoop would not have difficulties of setting up a cluster, setting up a framework. They could just use a vendor specific distribution with its cluster installation solutions, cluster management solution, and easily plan, deploy, install, and manage a cluster. So look into this link which talks about different distributions of Hadoop. Coming back, what is Hadoop? Hadoop is a open source framework for storing huge amount of data and processing it. It also depends on commodity machines and it does not need carrier class hardware. Now, when we say commodity machines, we are still talking about machines which are higher than a basic laptop or a basic server, but then they are not at the level of a carrier class hardware and costing huge to the organization. Hadoop as a framework has two main components, or I would say two processing layers. It has a storage layer which is called HDFS, Hadoop Distributed File System, and it has a processing layer which is called Yarn, which can handle different processing frameworks, in which Hadoop MapReduce is the oldest, most mature, and most evolved processing framework. HDFS derives its existence from GFS. It solves the issue of storing huge amount of data in a distributed fashion, and MapReduce is a programming model which allows to process data which is distributed across a cluster. We will learn on HDFS and MapReduce in further slides. HDFS is a storage layer. Now compare your laptop, compare your desktop. That also has a processing layer and a storage layer. Your disks are your storage layer. Your RAM and CPU core is your processing layer. Similarly, Hadoop as a solution has a storage layer, that is a distributed file system which can store huge amount of data in multiple machines instead of a single machine or a single server, which basically makes it highly reliable, highly fault tolerant, and distributed for parallel processing. Consider a data file of size 1 gigabyte. Now, if that was getting stored in one single machine, we would still have the data getting stored in one or multiple disks. And if you would try to read the data, the seek time taken to read the data would be very high in comparison to reading it from multiple machines. Now, HDFS, like your GFS, divides the file into smaller chunks and stores the data across the Hadoop cluster. In previous versions of Hadoop, the default block size was 64 MB. However, from Hadoop version 2 onwards, the block size is 128 MB. Now that's customizable depending on the average size of the data which is coming into the cluster. The block size can be changed. The minimum block size is 128 MB, which basically means that every file which is less than or equal to 128 MB would use one block, and any file which goes beyond the size of block will use multiple blocks, and these blocks would be residing on the underlying slave machines. Files are automatically split by Hadoop framework into blocks of default block size and stored across the cluster. Each node in your Hadoop cluster would have a bunch of disks that would be storing these blocks. Now, once we have the data stored in a distributed fashion, that also gives us the flexibility of going for distributed computing. And when we say distributed computing, we are talking about performing distributed parallel processing on large volumes of data. Take an example where we are talking about one single machine or one huge server which has 4 IO channels, and each input output channel can take care of 100 megabytes of per second, 100 megabytes of data per second. So if we have a data file of 1 terabyte, it would take approximately 43 minutes for one machine to process 1 terabyte of data. If you compare that with distributed computing, where we are talking about hundreds of machines, each machine having similar number of input output channels, and each channel having the same capacity to handle 100 megabyte of data per second, if a data file of 1 terabyte had to be processed in a parallel processing fashion using distributed computing, it would take just 26 seconds for 100 machines to process 1 terabyte of data in this environment. Now, all of you might be thinking that, yeah, this is right, but then what about the processing logic? That might be complicated. And yes, that would be, but then we have a MapReduce programming model and a processing framework to help us doing that. Now, when we look at one of the distributions of Hadoop, that is Hortonworks, it also has different resources that provide security to your big data. Now, before we start talking on these different services like Apache Knox, Apache Ranger, which basically allow you to monitor, authorize, and audit your Hadoop clusters, let's also look at the history of Hadoop, which started in 1999 with Apache Software Foundation. In 2002, where Nutch created by Doug Cutting and Mike Cafrella. Then Doug Cutting joined Hadoop and took Nutch product with him. 2008, Nutch was divided and Hadoop was born. And 2008, Yahoo released Hadoop as an open source project to ASF. In 2008, also Hadoop-based startup Cloudera Incorporated. Cutting left Yahoo for Cloudera. Yahoo was then coming out with Hortonworks as a commercial Hadoop distribution. MapR Technology also released Hadoop distribution. Greenplum released Hadoop distribution, and Pivotal HD. So this is a brief on history of Hadoop. You can always read about history of evolution of Hadoop, how it started, and today there are more than 10 distributions which are existing in market. However, Cloudera is the dominant one, and as per recent news items, Cloudera and Hortonworks have merged as one entity, which will bring up better solutions to the market. Now here we will want to learn on Hadoop ecosystem. So far we have learned on big data. So what is big data? We have learned on what are the different use cases where big data can be used, different organizations which use big data, and we took an example of Facebook. We also looked at Google File System, which laid the foundation for HDFS, the Hadoop's distributed file system. And we have not yet spoken about the processing layer, which is Yarn, and the processing framework, which is MapReduce, which we will discuss in future slides or further slides. Let's spend some time in understanding the Hadoop ecosystem, or you might have heard as ecosphere, which has various products, or you can say tools, or you can say packages which work together to comprise your Hadoop cluster. Now this picture shows the different components which are used for different requirements to work on your big data. Starting from bottom to top, we would look at HDFS, which is Hadoop distributed file system. Basically a file system which would use multiple machines to store the data. You have a processing layer, that is Yarn. We have a programming model, that is MapReduce, which could be written in any programming language, primarily in Java, but then that could be also written in Python or Scala or any other programming language. So these are the main components. So you have HDFS and you have Yarn. These are the processing layers, and for each processing layer we would have multiple processes which would be running on different machines within a cluster. Now what would a Hadoop cluster do if we did not have any data, and where would that data come from? So there might be a lot of sources where the data is getting generated, and that data might already be stored in RDBMS. And if you are interested in bringing in the structured data from your RDBMS layer to your Hadoop ecosystem, then you would use data ingestion tools like Sqoop. So Sqoop would be used for data ingestion, transformation, and pushing it into HDFS. Now that could also be used for exporting the data from HDFS back to RDBMS. but Sqoop mainly is for structured data. Now you have other data ingestion tools like Flume, which is used for ingestion of streaming or unstructured kind of data. Data could directly be ingested into HDFS, or it could be going into a data warehousing package called Hive. Now Hive is a data warehousing package on top of HDFS where users could write their SQL queries to process the data. They could be creating their tables and databases to store the data, and that data would eventually be getting stored in HDFS and then in the underlying systems. Hive could be accessed through various services, and HCatalog is one of them. Your data which is being ingested could also be stored in a unstructured data store such as Apache HBase. Now there are lots of NoSQL databases. There are a lot of data ingestion tools. So if we go to Google and if we search for data ingestion tools, if I say data ingestion tools, so you could look at this link which shows around 18 different data ingestion tools which are existing in market. You have these tools for import and export, for transforming, for governance, for even processing the data while the data is being ingested. So you have Apache Kafka, which is a publish subscribing messaging system. You have Apache NiFi, which is not only for streaming or structured data, but it also helps with governance. You have Wavefront, you have Data Torrent, Amazon's Kinesis, Apache Storm, Samza, SyncSort, Goblin, Flume, Sqoop, Samza, FluentD, Morphlins, White Elephant, Chukwa, Heka, Scribe, Databus, and many more. These are some data ingestion tools which can be used. Now we could also look at NoSQL databases, and if you just type in NoSQL databases, that can take you to nosqldb.org, and that would show you that there are more than 225 NoSQL databases existing in market. NoSQL stands for not only SQL. So these are databases which can be created without defining any schema. They could be key value stores, they could be document based databases which allow a lot of dynamism, which have different kind of constraints and can allow you to store your structured, unstructured or semi-structured data. So have a look at this exhaustive list of NoSQL databases. So coming back to your Hadoop ecosystem, your data could be ingested using one of the data ingestion tools into HDFS or into a Hive table or into Hive that would be using HDFS as the underlying layer. Your data could also be imported into a NoSQL databases such as HBase, which is a 4-dimensional database. It's a key value store which allows for faster random access across billions of records. We learn on HBase, on Hive in other sessions. Now, when you talk about Hadoop ecosystem, you could have a workflow manager such as Oozie. Now, there are other workflow managers like Azkaban, you have Luigi, right, which can be used, but Oozie comes with Hadoop. Now, not with Apache Hadoop. As I said, Apache Hadoop is an open source, and to set up an Apache Hadoop cluster and to set up Hive or HBase or any of these components, we would have to manually download the packages, edit the configs, set up the processes, and start the cluster and services. However, if you were using a vendor specific distribution, many of these packages would come as a packaged solution. So Oozie is a workflow scheduler which allows you to create a workflow of different jobs which could be run on a Hadoop cluster. You could have a service such as Zookeeper, which is mainly for management and monitoring. So it's a centralized coordination service, which especially plays a very important role when it is managing a high availability cluster of Hadoop or HBase. You have pig scripting, which allows for processing of data in a very concise way. You have Hive querying, which allows users to write their SQL queries to process the data. You could also do interactive analysis using packages like Apache Drill. You have Apache Mahout for machine learning. You have Kafka, Apache Storm, and even Spark, which can be used for streaming. Now Spark again has different components, and it is an in-memory computing framework which allows you to work on streaming data, structured data, graph-based data, and even machine learning algorithms. So Hadoop as such is a solution which allows organizations to work on big data and Hadoop ecosystem and the components which are involved, which can be part of your Hadoop ecosystem, are growing. So there can be lots and lots of other components which can be part of your Hadoop ecosystem, which can be overall used to store, process, capture, and analyze big data. This is where we come to a point where we should now start learning on Hadoop distributed file system, which allows you to store data in a distributed fashion. HDFS basically makes it easier for organizations to store huge amount of data. In previous session, we were learning on big data, its characteristics, what are organizations interested in when they talk about big data, and different use cases. Today, we will learn on Hadoop distributed file system, which is basically the logical storage layer for a Hadoop cluster. HDFS is fault tolerant, is reliable, and is scalable. So let's understand and learn on the working of HDFS, that is the logical storage layer for a Hadoop cluster. HDFS is a distributed file system which is designed to store large volumes of data on commodity machines. It is designed with a low cost hardware, and that is what I mean when I say commodity machines. So we could have a cluster of tens and hundreds and thousands of nodes which can still scale and accommodate huge volume of data. It provides access to data across multiple Hadoop clusters. It has a high fault tolerance and throughput, and HDFS stores data in multiple servers instead of a central server. Now earlier when we were discussing on how storing data on a single machine can lead to more read or processing times and basically lead to high seek time, that can be taken care by a distributed file system such as HDFS, which would rely on file systems of multiple machines which form your Hadoop cluster. Now let's understand how HDFS works. For example, we have a large file which is to be stored on HDFS. Now that file would be broken down into blocks, and the block size by default is 128 MB. These blocks would then be stored across different slave machines or different nodes which are responsible for storing data. HDFS has a default block size of 128 MB, which can be increased as per requirement. Now that could be in megabytes, gigabytes, terabytes, or even bigger than that. The default block size is 128 MB from Hadoop version 2 onwards, and your previous versions of Hadoop had the block size of 64 MB. Here the point to be remembered is block is a logical entity which basically takes the data and stores it on the underlying machines in their disks. Now this is how it would look. In a normal Hadoop cluster, we would have one single master unless it is a high availability cluster where we could have multiple masters, that is two masters, one being active and one being standby. In a normal Hadoop cluster, you would have one master and multiple slave nodes where these data blocks are getting stored. Now, before we understand the MapReduce algorithm, let's also understand the working of HDFS and how data gets stored. Overall, how does it work? So let me just open up a notepad file and I would explain about HDFS. Now let's imagine that this is, I would like to have say 5 machines which could be forming my cluster. So I would have machine 1, machine 2, machine 3, machine 4, and machine 5. Now if I say my Hadoop cluster is running on these machines, which could be of a Apache Hadoop core distribution or having a vendor specific distribution such as Cloudera or Hortonworks or MapR or IBM Big Insight, etc. So these are some vendor specific distributions of a Hadoop cluster. Now here we can discuss later on how or what processes would be running on these machines. Now in case of Apache Hadoop cluster, to have a Hadoop cluster running, we would have to download the Hadoop related packages. We would have to untar, then we would have to edit config files to specify which processes would run on which nodes, and then basically we would be formatting HDFS, and then onwards we can go ahead and start our cluster. So it looks like in Apache Hadoop cluster we would have to manually do various things such as downloading the Hadoop related tar file, untarring it, editing the config files, formatting HDFS, and then going ahead and starting your cluster. In case of a vendor specific distribution such as Cloudera or Hortonworks, let me split it here. So you would have basically a cluster management solution that would help you in doing various things to set up your cluster. In case of a Cloudera distribution of Hadoop, you would have a Cloudera installer file, and then you would have a Cloudera manager which will help in deploying a Cloudera cluster. So downloading Hadoop related parcels or packages, untarring them, editing config files, formatting HDFS, and basically starting your cluster would be taken care automatically by Cloudera manager. In case of Hortonworks data platform, it would be Ambari software that would be used for deploying your cluster. Now, no matter which distribution of Hadoop you would be running, you would still have the same roles or processes which would be running. Let me just briefly discuss here about the terminologies. So let me bring up a file here which could explain these details. So let's look at this. Now here I have documented how it would look in different distributions of Hadoop. So we have Hadoop version 1 and 2, and let me just look for files. Yeah, so this is the one. Now if you would look in version 1 Apache Hadoop, we would call daemons or processes, and if you look at the names, we have the name node, we have data nodes, we have job tracker, we have secondary name node, and we have task trackers. In case of version 2, you would still call them daemons. You could have one or multiple name nodes. If it was a federation or a high availability kind of setup, you would have data nodes. Instead of job tracker, you would have resource manager, and then there is a temporary daemon called MR app master. If you had a high availability, then secondary name node would not be allowed, and if there was a federation kind of setup, secondary name node would still be existing. Instead of task trackers, you would have node managers. Now in case of vendor specific distributions such as Cloudera, whether you are talking about older version or newer version which is 5 point something, you would have what we call as roles. So in Apache Hadoop we call them daemons, in Cloudera we call them roles, in Hortonworks we call them components, but we are talking about the same thing. In case of Cloudera, you would have services which would be part of the cluster such as Impala, Oozie, Spark, Hive, HBase, Storm, Hue, HDFS, MapReduce, Yarn, and so on. Similarly, in Hortonworks also, you would have these services which would be running. In case of Apache Hadoop, we would not have so-called services seen, but then the functionality still exists. And how is that? That is depending on these daemons. So basically, if you look in Apache Hadoop or Cloudera or Hortonworks, everywhere we have these daemons, and we have these would be running on one or multiple nodes. So we could have different kind of setups, and just to briefly discuss on that, so we could have a name node running here, a resource manager running here, and you could have a secondary name node. Now don't go by name, it's not a second name node, we'll discuss about that later, a secondary name node. And then we could have data nodes running in machines. So this is one kind of setup where I'm talking about data node, node manager, and here we have a data node, node manager, and similarly we would have that on one more machine. Now this is one kind of setup. This is not the only setup possible. You could have a different setup where on the same machines you could decide to have data node and node manager running on every node. However, that would not be preferred because you wouldn't want the slaves and the masters to run on the same machine. However, this setup is also possible. You could have a high availability kind of setup, which basically is good for cluster and for an organization, where you could have name node 1 which would be running here, and say we can have a name node 2 running here. We could have a resource manager 2 running here, and then we could have a resource manager 1 running here, and I could still have my data node and node manager running in the same fashion. Now this would not be allowed in a high availability cluster because we have a standby name node. So this is one more setup which is possible. And then you could have a single node setup which could be everything having on the same machine, that is name node, resource manager, secondary name node, data node, and node manager. So these are different setups, and if somebody asks which is a preferable setup, then I would still go for either this one which has multiple data nodes and node managers, not this one, or your high availability setup. Now a single node or a pseudo distributed cluster is basically good for testing or some development kind of activities, and these are your distributed clusters. Now if we closely see, we basically have the roles or components or daemons running on these machines to take care of mainly two functionalities or two services, that is your HDFS, which is your storage layer, and yarn, which is your processing layer. So in a Hadoop cluster, we have a storage layer and we have a processing layer. For storage layer, that is HDFS, you basically have one single master and you have multiple slave processes running. So I could say for HDFS to work fine, I should have a name node running, multiple data nodes running, and then a secondary name node running. For yarn as a service, that is my processing layer, I would need minimum one resource manager and multiple node managers running on one or multiple machines. So these are the two layers, one being the storage layer and one being the processing layer. And for your storage layer, you have these processes wherein your name node is the master and your data nodes and secondary name node can be considered as the slaves. You have your resource manager as the master for your processing layer, and node managers are the slaves. Now this is briefly about the setup which could be in a particular environment. Now say the Hadoop related packages or parcels have been downloaded, whether it is a vendor specific distribution or Apache Hadoop cluster. Say untarring of that is done, editing of config files is done, formatting is done, and your cluster is started. In that case, your cluster would be up and running, and then we could basically have, and once your cluster is up, we would have the HDFS up and running, ready to allow us to store data. Now let's imagine that this is my HDFS which is up and running, or HDFS as a service is up and running. Let's imagine that these are my nodes, which is M1, M2, M3, M4, and M5. Now while the config files were edited for each of these nodes, it would have been defined which processes will run, and we would have also given path where these processes will store the data. So let's say that this is my M1, this is M2, M3, M4, and M5. M3, M4, and M5 have data nodes running. So we would have defined a path. Let's call it, say, ABC slash data, ABC slash again data, or D, and ABC. So this is the path which has been defined on every node to store Hadoop related data. And on M1, where we would have name node running, we would have still defined a path. Let's call it ABC slash N, where name node could store its data. So once your cluster is up and running and in your HDFS is available, we can have our data stored on HDFS. Now let's understand how does that work. So any client or an application which would want to write data to the cluster needs to interact with the master to begin with. Let's say client, machine, or an API or an application would be interested in writing the data. Now how would name node know about available data nodes? So as soon as the cluster comes up, the first thing which happens is these data nodes would be sending in their heartbeat to the name node every 3 seconds. So data nodes send the heartbeat to name node every 3 seconds to let the name node know, to let the master know that they are available. What does name node do with this? Name node is building a metadata in its RAM. So it already has some metadata in the disk, which was created as a result of formatting HDFS. And now we would have metadata in RAM, which is getting built. So initially, name node would have information of which data nodes are available in the cluster. Now, if a client or an application wants to write data to the cluster, it gets in touch with the name node, inquiring about the slave machines or inquiring about the data nodes where the data can actually be written. Your name node refers to the metadata collected so far and responds back mentioning the data nodes or the slave machines which are available for data storage. Based on this response, your client takes the file to HDFS, intending to write it to the cluster. Now in Hadoop, we basically have two things. One is the default block size, which we discussed earlier, is 128 MB. So you have 128 MB as the default block size, which is customizable and that can be changed depending on the average data size. And you have the default replication, which is 3. Now imagine the application or API or client would want to write a file which is 256 MB, which is bigger than the block size, and this file has to be broken down into what we call as blocks, which are logical entities. So the file is taken to the framework. Framework will split the file into blocks. So let's imagine that this file is 256 MB. It will be broken down into two blocks, B1 and B2, and these blocks will then be randomly distributed to the slave machines, that is the data nodes. So we would have block 1, say, getting stored here. Now you could also have block 1 getting stored on any of these data nodes. So we would have block 1 and then we could have block 2, which could be written here, and then you would also have their replicas sitting on the machine. So the rule of replication is you will never have two identical blocks sitting on the same node. So if I have block 1 here, then I will never have a replica of block 1 again on the same machine. So we will have a replica of block 2 here, block 1 here, and you have a replica of block 2 here. There is no differentiation between which one is the original and which one is the replica. For the cluster, all the blocks are same. And what also happens is, after the blocks are written, your data nodes are repeatedly sending their block report to name node every 10 seconds. And this information is again updated in the name node's metadata. So now name node will have information what are the files. The files are broken down into what blocks. The blocks are residing on which data nodes. And this metadata is getting built in the name node as data nodes respond with their heartbeats and also every 10 seconds with their block report. Now we need to remember one point here, that name node is basically a master and data nodes are the slave. Hadoop as a framework has been coded in Java, which basically means that every directory, every file and file related block is considered as an object which is getting stored. And for every object which name node is tracking, 150 bytes of name node's RAM is utilized, which also tells us that if the block sizes were smaller than 128 MB, then for the same file we would have more number of blocks, which would mean that name node's RAM would be overutilized and overload name node. So block size has to be chosen with a lot of consideration on the master's RAM and what is the average size of the data. Now this is how the data is distributed in blocks and distributed across the data nodes. Thus HDFS is very fault tolerant, because if any of the data nodes fail, then you still have other data nodes which have the replica of data, thus making it possible to read the data and access the data even if multiple data nodes go down. Now there are other internals, that is how data nodes are placed in racks or what has rack awareness to do in block placement, but we will learn on all that later. So this is how your HDFS works. Now there are many other things such as the read and write process, which is taken care by your methods such as open and create, which internally are playing a role when a read or write operation happens. Also, facts like replication is a sequential process, but write activity is parallel. So we can learn more functionality of HDFS in later sessions, but this is in brief on how HDFS works, how your file is split into blocks, and the blocks are getting stored on the disks. Note that the block contains the data. So even if you have a file which is 1 kilobyte, and if this file is to be stored on HDFS, it will still use a block of 128 MB, which does not mean that there is a disk space getting wasted. When the block resides on the data node's disk, it will only occupy 1 kilobyte of space for the data it has, which means that block is a logical entity to take your data to the disk and get it stored on the disk. This is how your HDFS works and basically takes care of reliable data storage across machines in distributed fashion. Now that we have set up a 2-node cluster which has 2 data nodes, 2 node managers, 1 master machine, let's try working with HDFS. Let's look at quick commands which allow you to write data to the cluster, although there are different ways. The first way is using commands. The second is using an IDE, and where you could write your code to use Hadoop's file system API. And the third is a graphical user interface called Hue, which normally does not come with Apache, although it can work with Apache. It comes as a service with Cloudera and other distributions. To work with HDFS, we need some sample data. Now there are various websites from where you can get some sample data. So you can open up your browser and let me show you some sample places or sample data set links from where you can download bigger or smaller files, which then can be used to write data to your HDFS. Although you could just pick up a local file, or you could create your own files and write them to HDFS. There are various dataset sites which can be used. So for example, you can type in machine learning UCI datasets, and this is one link which has more than 200 datasets which can be used for even data science kind of activities, which can be used for testing with your algorithms, and you can download data from here onto your local machine, and then from your local machine we will be writing the data to HDFS, which then based on the size of the data splits the data into blocks, and your blocks would get stored on your underlying machines wherever data nodes run. So I can click on this UCI machine learning repository, or even just on data sets to be very specific. All we need is some sample data sets. You can get Kaggle data sets, you can get data sets from Yelp website which are bigger data sets zipped, and you can be using them to write data to see how your file split into multiple blocks. Now here we have a lot of data. We can click on any one link to begin with, and here I have the data folder, shows me the some file, and I can just right click on this, save link as, and save the file. This is a simple text file and we can save it. And you can get various data sets from here. You can even go to Yelp dataset challenge, and that has bigger files which are zipped and they can be downloaded. So you can click on download dataset. Although I will not start the downloading here, you can just give in your name here, just some email ID, some initials, and you can click on download. So this is one more website where you can download the JSON datasets, which are 3.6 gigabytes in compressed format, and then you have photos which are in 7.2 gigabytes. You can also say Gutenberg download books, and that is again a website from where you can download free datasets which are not very huge. So try to get some variety of datasets in different formats which then you can write to HDFS. You can even use your HDFS log files which already exist on your machines, and you don't need to download anything from internet. Now let's close this for now. So I already have some file. Let's copy this from home, HDC downloads. That was my file. Let's copy it to home HDC, and here's my file. I can check the permissions. So that's owned by HDC. I can even look into user local Hadoop logs, and there are some already log files. So you can even copy some of these files using copy user local Hadoop logs, and let's take Hadoop data node related log, and let's copy it to home SDC for our testing. And now we have some other files. Now to work with HDFS, as I said, you can always type in HDFS and that shows you various options. Now we already used the first option, which is name node hyphen format. We also used HDFS admin to look at how many nodes we have, and to work with your HDFS file system, the option is DFS. So you would say HDFS, DFS, and then you can always hit on enter, which shows you various options to work with your distributed file system, like creating a directory, copying some files, getting data from your HDFS to your local machine, changing the permissions, changing the replication, and many other options. So here, let's click on HDFS, DFS. Let's create a directory and let's call it my data. So this is a directory I'm creating on HDFS. Remember, this directory will not be seen on your local machine. It is a HDFS directory. Now, if I look in my root, I don't see my data because that's a HDFS directory which is technically getting created on HDFS. And once you start writing data to HDFS, the relevant blocks will start getting stored under abc/data. So as of now, we can always keep a browser open to see, as we work with HDFS, how does the data propagate or come to your distributed file system using the web interface. So here, let's say http://m1.5.0.0.70, and that's my browser interface. Let's click on utilities and let's click on browse the file system, which should show the directory which we have created, although that does not have any data as of now. Let's go in here. And now we know that we have some files here. So I will say HDFS, DFS, and this has two options. Either I can say put or I can say copy from local. Both of these do the same thing, and both of these you can find here. So we have put and we should have copy from local. That is, you're copying the data from your local machine to your HDFS. So now I will say copy from local. I will say take the ABA directory or file and put it in my data. So now I'm technically copying a file from my local file system to my HDFS, which is then using again my local file system's path. So this is done. Let's quickly check by clicking on my data if my file is written. Now if you see, this file is 187 kilobytes. However, this will still use a block of 128, and in my previous sessions I already explained why a block of 128, but when it goes to the disk, it will only occupy the space for the data the block has. We can quickly go in here and we can do a HDFS DFS listing of my directory, which should have my file now, and we can quickly check if my file is replicated either using the web interface, which says replication is 2. That means the file related blocks should be getting stored on the underlying data nodes. We can always click on overview if we would want to browse and scroll down, which says there are 3 files and a directory. The file has 1 block, so totally you have 4 file system objects. We can scroll down to show or see we have 2 live nodes, and if you see, each node has 1 block. We can always look from our data path by looking into abc/data/current, that has block pool directory, that has current, that has finalized, that has subdirectory, and the block. Look at the size of the block. It is 191, which relates to the kilobyte size which we are talking about. Similarly, we can check on M2 machine, which also has a data node running, to make sure our file related block is replicated. So look in block pool, current, finalized, subdirectory, and that shows me the same block which is replicated with its meta file and with the same size. This ensures that my data is getting replicated as per whatever factor we have set, and my file is written to HDFS. And now I can also do a complete listing. I can just say a recursive listing to show me all the directories and all the files which I have in my HDFS. I think we are forgetting something. We are logged in as root. which is not right. So we need to be logged in as HTC, and then we can try our commands, that is HDFS dfs-ls slash, which should show me my directory. But then if you would want to do a recursive listing of showing all the directories and files, you can just add -r. So we have written a file to HDFS in my data directory. Similarly, I can write using a put command. Last time we used a copy from local. I will use a put command. I will say, let's take this log file and let us write it to the my data directory. Instead of copy from local, I'm using a put command, which also allows me to write the file to my HDFS. Once this is done, let's go to the web UI and let's go to browse the file system. Let's look in our directory, and that shows me that I have a log file which is even smaller than the first file which we wrote. It is in kilobytes. However, it is replicated. It is using still the block size, and we can always go back and look at the terminal to see if for my new file I have a new block which should be in my data path. And if you see this is my block, which will also have a replication on machine 2. So this is how you write one file, or you could write multiple files. Let's create some files here. So I have these log files. Let's say Hadoop log, and let's give it a name like this. So now if you see, I just created multiple files, and I can also say HDFS dfs make directory, let's say my data 2. So I'm creating a new directory on my HDFS, and then I can even copy multiple files or a complete directory. So all I need to do here is give a matching pattern or a directory. So I'll say HDFS dfs put, and then I can say take all the directories of files and put it to my data 2. Remember, this one file or multiple files are following the replication what has been set at a cluster level. Now if we do a recursive listing where I would want to see all the directories and the files which are within my HDFS, I see that I have a my data directory, and I also have a my data 2 directory which has multiple files, and all of the files within the directory are following the replication set at a cluster level. So all of them are having their blocks replicated twice. We can always go back here. We can just do a back, and that shows me what I have in my data 2. Everything is replicated twice. What I have in my data is also replicated twice. Now HDFS also has a functionality where you can write data with a different replication. So let's create one more directory, and now let's write data with a different replication. So the way I write my files, I follow the same thing. However, now I will say -dfs.replication, and I will specify it as 1. So I'm passing in as argument, and I'm specifying that I would want to write data with a replication of just 1. So my blocks will not be considered under replicated, and I'm choosing to write these files in this directory with a replication of 1. We can check from our browser interface by just doing a quick refresh. And here, if I click on my data 3, it shows it follows a replication of 1. There is also a command to check your replication status using HDFS. So we can say HDFS fsck/files/blocks, and if I would want to see only blocks or only files, I could choose one of them. Now here I have given a complete HDFS file system. I can replace that with /my-data. So I can say my data 3. This is what I would want to see, and this will show me within this directory how many files I have, how many blocks does each file use, and is it replicated correctly. So my fsck command gives me an information that in my data 3 I have one file which is 24 kilobytes, uses one block because it is very smaller than 128, and it is replicated only once. So there is no situation of over under misreplicated blocks. We have our files correctly replicated as they were specified while writing. Same thing can be seen for other files, say my data 2, and that will tell me that all the files within my data 2 were replicated as per the default replication which was at a cluster level. And if you see here, everything is replicated twice. We don't have any over, under, misreplicated blocks, and my file system status is healthy. So this is the HDFS command to make sure that your files are replicated correctly. So we have seen how your files are written with default replication. We have seen how your files follow a dynamic replication, what you specify on the command line. Now we can also see a command which allows us to change replication after the data has been written. So I can say set rep, and I can say path, that is my data 3, where I initially had all my file related blocks replicated only once, and now I'll say my data 3, and I can specify that this should follow a replication of 2, which basically means that it will look into the directory, it will check all the files which had only one block, and now it will create a replica of those blocks across other data nodes. We can always go back and look into the data node logs to see the replication happening. We can also look from the browser interface, which initially was showing a replication of 1, and now it shows a replication of 2. So this is the command to change the replication after the data has been written. So our writes can have default replication. We can write files with a different replication. We can change the replication after the data is written. Not only that, we can even get the data from our HDFS to my local machine. And for that, I'll give HDFS get command or copy to local. So I can say my data 3, and then I can bring it to my local machine in home HDC using a get command. So this is to get data from your HDFS to your local machine using a HDFS command. Now if you see, I should have a my data 3 directory which is in my local path, and we can look in my data 3. It has all the files which we had on HDFS. So we were not only putting data from our local machine to HDFS, we also successfully brought data from our HDFS to local machine. We have written data with different replication. We have checked the status of nodes. We have checked the status of blocks, and if we would want to delete some data, HDFS also has options for that. So I can say HDFS DFS remove, and I could also do a recursive remove to remove everything including the directory from my data 3. So this will delete data from my HDFS. However, if thrash is enabled, now thrash basically means recycle bin, which depends on a property in the core-site file. We have not enabled it. If thrash is enabled, then your data will be deleted from HDFS. However, it will not be permanently deleted. It will sit in thrash for a time interval, what admin has specified in the configuration file. So right now I deleted thrash, and this seems to be gone from HDFS because we have not set up any thrash. However, if a thrash is set up, then either you can decide to have your data deleted and still be in thrash so that it could be restored, or you could delete it permanently using a skip thrash option. However, remember, this skip thrash option makes more sense if the thrash is enabled in your cluster and you do not want your deleted data to be sitting in thrash even for whatever time interval has been set. Because even if the data sits in thrash and your thrash is a directory structure on HDFS, all the data will still be replicated. So we have seen how you can write data to the cluster, how you can get data from cluster to your local machine, how you can write it with different replications, how you can delete it from your cluster, and do a recursive listing of your directories and files. Now there are various other commands which can be used. For example, something like copy or move or change permissions and many more.
Thanks, Ajay. Now we have Richard and Ajay taking us through the Hadoop ecosystem. We will look into HDFS, MapReduce, Yarn, Sqoop, Hive, Pig, and HBase.
Suppose you have a library that has a collection of huge number of books on each floor, and you want to count the total number of books present on each floor. What would be your approach? You could say, I will do it myself, but then don't you think that will take a lot of time? And that's obviously not an efficient way of counting the number of books in this huge collection on every floor by yourself. Now, there could be a different approach or an alternative to that. You could think of asking 3 of your friends or 3 of your colleagues, and you could then say if each friend could count the books on every floor, then obviously that would make your work faster and easier to count the books on every floor. Now, this is what we mean by parallel processing. So when you say parallel processing in technical terms, you're talking about using multiple machines, and each machine would be contributing its RAM and CPU cores for processing, and your data would be processed on multiple machines at the same time. Now, this type of process involves parallel processing in our case, or in our library example, where you would have person 1 who would be taking care of books on floor 1 and counting them, person 2 on floor 2, then you have someone on floor 3 and someone on floor 4. So every individual would be counting the books on every floor in parallel, so that reduces the time consumed for this activity. And then there should be some mechanism where all these counts from every floor can be aggregated. So what is each person doing here? Each person is mapping the data of a particular floor, or you can say each person is doing a kind of activity or basically a task on every floor, and the task is counting the books on every floor. Now then you could have some aggregation mechanism that could basically reduce or summarize this total count, and in terms of MapReduce, we would say that's the work of reducer. So when you talk about Hadoop MapReduce, it processes data on different node machines. Now this is the whole concept of Hadoop framework, right? That you not only have your data stored across machines, but you would also want to process the data locally. So instead of transferring the data from one machine to other machine, or bringing all the data together into some central processing unit and then processing it, you would rather have the data processed on the machines wherever that is stored. So we know in case of Hadoop cluster, we would have our data stored on multiple data nodes on their multiple disks, and that is the data which needs to be processed. But the requirement is that we want to process this data as fast as possible, and that could be achieved by using parallel processing. Now, in case of MapReduce, we basically have the first phase, which is your mapping phase. So in case of MapReduce programming model, you basically have 2 phases. One is mapping and one is reducing. Now, who takes care of things in mapping phase? It is a mapper class. And this mapper class has the function which is provided by the developer, which takes care of these individual map tasks which will work on multiple nodes in parallel. Your reducer class belongs to the reducing phase. So a reducing phase basically uses a reducer class which provides a function that will aggregate and reduce the output of different data nodes to generate the final output. Now that's how your MapReduce works, using mapping and then obviously reducing. Now you could have some other kind of jobs which are map only jobs wherein there is no reducing required, but we are not talking about those. We are talking about our requirement where we would want to process the data using mapping and reducing, especially when data is huge, when data is stored across multiple machines, and you would want to process the data in parallel. So when you talk about MapReduce, you could say it's a programming model. You could say internally it's a processing engine of Hadoop that allows you to process and compute huge volumes of data. And when we say huge volumes of data, we can talk about terabytes, we can talk about petabytes, exabytes, and that amount of data which needs to be processed on a huge cluster. We could also use MapReduce programming model and run a MapReduce algorithm in a local mode. But what does that mean? If you would go for a local mode, it basically means it would do all the mapping and reducing on the same node using the processing capacity, that is RAM and CPU cores, on the same machine, which is not really efficient. In fact, we would want to have our MapReduce work on multiple nodes, which would obviously have mapping phase followed by a reducing phase, and intermittently there would be data generated. There would be different other phases which help this whole processing. So when you talk about Hadoop MapReduce, you are mainly talking about 2 main components or 2 main phases, that is mapping and and reducing, mapping taking care of map tasks, reducing taking care of reduced tasks. So you would have your data which would be stored on multiple machines. Now when we talk about data, data could be in different formats. We could, or the developer could specify what is the format which needs to be used to understand the data which is coming in. That data then goes through the mapping. Internally there would be some shuffling, sorting, and then reducing, which gives you your final output. So the way we access data from HDFS, or the way our data is getting stored on HDFS, we have our input data which would have one or multiple files in one or multiple directories, and your final output is also stored on HDFS to be accessed, to be looked into, and to see if the processing was done correctly. So this is how it looks. So you have the input data which would then be worked upon by multiple map tasks. Now how many map tasks, that basically depends on the file, that depends on the input format. So normally we know that in a Hadoop cluster you would have a file which is broken down into blocks depending on its size. So the default block size is 128 MB, which can then still be customized based on your average size of data which is getting stored on the cluster. So if I have really huge files which are getting stored on the cluster, I would certainly set a higher block size so that my every file does not have huge number of blocks creating a load on name nodes RAM, because that's tracking the number of elements in your cluster or number of objects in your cluster. So depending on your file size, your file would be split into multiple chunks, and for every chunk we would have a map task running. Now what is this map task doing? That is specified within the mapper class. So within the mapper class you have the mapper function which basically says what each of these map tasks has to do on each of the chunks which has to be processed. This data intermittently is written to HDFS where it is sorted and shuffled, and then you have internal phases such as partitioner which decides how many reduce tasks would be used or what data goes to which reducer. You could also have a combiner phase which is like a mini reducer doing the same reduce operation before it reaches reduce. Then you have your reducing phase which is taken care by a reducer class, and internally the reducer function provided by developer which would have reduce task running on the data which comes as an output from map tasks. Finally, your output is then generated which is stored on HDFS. Now in case of Hadoop, it accepts data in different formats. Your data could be in compressed format, your data could be in Parquet, your data could be in Avro, text, CSV, TSV, binary format, and all of these formats are supported. However, remember, if you're talking about data being compressed, then you have to also look into what kind of splittability the compression mechanism supports. Otherwise, when MapReduce processing happens, it would take the complete file as one chunk to be processed. So HDFS accepts input data in different formats. This data is stored in HDFS, and that is basically our input, which is then passing through the mapping phase. Now what is mapping phase doing? As I said, it reads record by record. Depending on the input format, it reads the data. So we have multiple map tasks running on multiple chunks. Once this data is being read, this is broken down into individual elements. And when I say individual element, I could say this is my list of key value pairs. So your records based on some kind of delimiter or without delimiter are broken down into individual elements, and thus your map creates key value pairs. Now these key value pairs are not my final output. These key value pairs are basically a list of elements which will then be subjected to further processing. So you would have internally shuffling and sorting of data so that all the relevant key value pairs are brought together, which basically benefits the processing. And then you have your reducing, which aggregates the key value pairs into set of smaller tuples or tuples, as you would say. Finally, your output is getting stored in the designated directory as a list of aggregated key value pairs, which gives you your output. So when we talk about MapReduce, one of the key factors here is the parallel processing which it can offer. So we know that our data is getting stored across multiple data nodes, and you would have huge volume of data which is split and randomly distributed across data nodes, and this is the data which needs to be processed. And the best way would be parallel processing. So you could have your data getting stored on multiple data nodes or multiple slave nodes, and each slave node would have again one or multiple disks. To process this data, basically we have to go for parallel processing approach. We have to use the MapReduce. Now let's look at the MapReduce workflow to understand how it works. So basically you have your input data stored on HDFS. Now this is the data which needs to be processed. It is stored in input files, and the processing which you want can be done on one single file, or it can be done on a directory which has multiple files. You could also later have multiple outputs merged, which we achieve by using something called as chaining of mappers. So here you have your data getting stored on HDFS. Now input format is basically something to define the input specification and how the input files will be split. So there are various input formats. Now we can search for that. So we can go to Google and we can basically search for Hadoop, MapReduce, Yahoo tutorial. This is one of the good links. And if I look into this link, I can search for different input formats and output formats. So let's search for input format. So when we talk about input format, you basically have something to define how input files are split. So input files are split up and read based on what input format is specified. So this is a class that provides following functionality. It selects the files or other objects that should be used for input. It defines the input split that break a file into tasks, provides a factory for record reader objects that read the file. So there are different formats if you look in the table here, and you can see that the text input format is the default format, which reads lines of a text file, and each line is considered as a record. Here the key is the byte offset of the line, and the value is the line content itself. You can have key value input format, which parses lines into key value pairs. Everything up to the first tab character is the key, and the remainder is the line. You could also have sequence file input format, which basically works on binary format. So you have input format, and in the same way you can also search for output format, which takes care of how the data is handled after the processing is done. So the key value pairs provided to this output collector are then returned to output files. The way they are written is governed by output format. So it functions pretty much like input format as described in earlier, right? So we could set what is the output format to be followed, and again you have text output, sequence file output format, null output format, and so on. So these are different classes which take care of how your data is handled when it is being read for processing, or how is the data being written when the processing is done. So based on the input format, the file is broken down into splits, and this logically represents the data to be processed by individual map tasks, or you could say individual mapper functions. So you could have one or multiple splits which need to be processed depending on the file size, depending on what properties have been set. Now once this is done, you have your input splits which are subjected to mapping phase. Internally you have a record reader which communicates with the input split and converts the data into key value pairs suitable to be read by mapper. And what is mapper doing? It is basically working on these key value pairs, the map task, giving you an intermittent output which would then be forwarded for further processing. Now once that is done and we have these key value pairs which is being worked upon by map, your map tasks as a part of your mapper function are generating your key value pairs, which are your intermediate outputs to be processed further. Now you could have, as I said, a combiner phase, or internally a mini reducer phase. Now combiner does not have its own class. So combiner basically uses the same class as the reducer class provided by the developer, and its main work is to do the reducing, or its main work is to do some kind of mini aggregation on the key value pairs which were generated by map. So once the data is coming in from the combiner, then we have internally a partitioner phase which decides how outputs from combiners are sent to the reducers. Or you could also say that even if I did not have a combiner, partitioner would decide based on the keys and values, based on the type of keys, how many reducers would be required or how many reduce tasks would be required to work on your output which was generated by map task. Now once partitioner has decided that, then your data would be then sorted and shuffled, which is then fed into the reducer. So when you talk about your reducer, it would basically have one or multiple reduce tasks. Now that depends on what partitioner decided or determined for your data to be processed. It can also depend on the configuration properties which have been set to decide how many reduce tasks should be used. Now internally all this data is obviously going through sorting and shuffling so that your reducing or aggregation becomes an easier task. Once we have this done, we basically have the reducer, which is the code for the reducer is provided by the developer, and all the intermediate data has then to be aggregated to give you a final output, which would then be stored on HDFS. And who does this? You have an internal record writer which writes these output key value pairs from reducer to the output files. Now this is how your MapReduce works, wherein the final output data can be not only stored but then read or accessed from HDFS or even used as an input for further MapReduce kind of processing. So this is how it overall looks. So you basically have your data stored on HDFS. Based on input format, you have the splits, then you have record reader, which gives your data to the mapping phase, which is then taken care by your mapper function. And mapper function basically means one or multiple map tasks working on your chunks of data. You could have a combiner phase, which is optional, which is not mandatory. Then you have a partitioner phase which decides on how many reduce tasks or how many reducers would be used to work on your data. Internally there is sorting and shuffling of data happening, and then basically based on your output format, your record reader will write the output to HDFS directory. Now internally you could also remember that data is being processed locally, so you would have the output of each task which is being worked upon stored locally. However, we do not access the data directly from data nodes, we access it from HDFS, so our output is stored on HDFS. So that is your MapReduce workflow. When you talk about MapReduce architecture, now this is how it would look. So you would have basically an edge node or a client program or an API which intends to process some data. So it submits the job to the job tracker, or you can say resource manager in case of Hadoop Yarn framework, right? Now before this step, we can also say that an interaction with name node would have already happened, which would have given information of data nodes which have the relevant data stored. Then your master processor. So in Hadoop version 1 we had job tracker, and then the slaves were called task trackers. In Hadoop version 2, instead of job tracker you have resource manager, and instead of task trackers you have node managers. So basically your resource manager has to assign the job to the task trackers or node managers. So your node managers, as we discussed in Yarn, are basically taking care of processing which happens on every node. So internally there is all of this work happening by resource manager, node managers, and application master, and you can refer to the Yarn based tutorial to understand more about that. So here your processing master is basically breaking down the application into tasks. What it does internally is once your application is submitted, your application to be run on Yarn processing framework is handled by resource manager. Now forget about the Yarn part as of now. I mean, who does the negotiating of resources, who allocates them, how does the processing happen on the nodes, right? So that's all to do with how Yarn handles the processing request. So you have your data which is stored in HDFS, broken down into one or multiple splits depending on the input format which has been specified by the developer. Your input splits are to be worked upon by your one or multiple map tasks which will be running within the container on the nodes. Basically, you have the resources which are being utilized. So for each map task, you would have some amount of RAM which will be utilized, and then further the same data which has to go through reducing phase, that is your reduce task, will also be utilizing some RAM and CPU cores. Now internally you have these functions which take care of deciding on number of reducers, doing a mini reduce, and basically reading and processing the data from multiple data nodes. Now this is how your MapReduce programming model makes parallel processing work, or processes your data which is stored across multiple machines. Finally, you have your output which is getting stored on HDFS. So let's have a quick demo on MapReduce and see how it works on a Hadoop cluster. Now we have discussed briefly about MapReduce, which contains mainly two phases, that is your mapping phase and your reducing phase. And mapping phase is taken care by your mapper function, and your reducing phase is taken care by your reducer function. Now in between we also have sorting and shuffling, and then you have other phases which is partitioner and combiner, and we will discuss about all those in detail in later sessions. But let's have a quick demo on how we can run a MapReduce which is already existing as a package jar file within your Apache Hadoop cluster or even in your Cloudera cluster. Now we can build our own MapReduce programs, we can package them as jar, transfer them to the cluster, and then run it on a Hadoop cluster on Yarn, or we could be using already provided default programs. So let's see where they are. Now these are my two machines which I have brought up, and basically this would have my Apache Hadoop cluster running. Now we can just do a simple start -all.sh. Now I know that this script is deprecated and it says instead use start DFS and start yarn, but then it will still take care of starting of my cluster on these two nodes, where I would have one single name node, two data nodes, one secondary name node, one resource manager, and two node managers. Now if you have any doubt in how this cluster came up, you can always look at the previous sessions where we had a walkthrough in setting up a cluster on Apache, and then you could also have your cluster running using less than 3 GB of your total machine RAM, and you could have an Apache cluster running on your machine. Now once this cluster comes up, we will also have a look at the web UI which is available for name node and resource manager. Now based on the settings what we have given, our UIs will show us details of our cluster, but remember the UI is only to browse. Now here my cluster has come up. I can just do a JPS to look at Java related processes, and that will show me what are the processes which are running on C1, which is your data node, resource manager, node manager, and name node. And on my M1 machine, which is my second machine which I've configured here, I can always do a JPS, and that shows me the processes running, which also means that my cluster is up with two data nodes with two node managers. And here I can have a look at my web UI. So I can just do a refresh, and the same thing with this one, just do a refresh. So I had already opened the web pages. So you can always access the web UI using your name node's host name and 570 port. It tells me what is my cluster ID, what is my block pool ID. It gives you information of what is the space usage, how many live nodes you have, and you can even browse your file system. So I have put in a lot of data here. I can click on browse the file system, and this basically shows me multiple directories, and these directories have one or multiple files which we will use for our MapReduce example. Now if you see here, these are my directories which have some sample files, although these files are very small, like 8.7 kilobytes. If you look into this directory, if you look into this, I have just pulled in some of my Hadoop logs and I have put it on my HDFS. These are a little bigger files, and then we also have some other data which we can see here, and this is data which I've downloaded from web. Now we can either run a MapReduce on a single file or in a directory which contains multiple files. Let's look at that. Before looking a demo on MapReduce, also remember MapReduce will create a output directory, and we need to have that directory created. Plus we need to have the permissions to run the MapReduce job. So by default, since I'm running it using admin ID, I should not have any problem. But then if you intend to run MapReduce with a different user, then obviously you will have to ask the admin, or you will have to give the user permission to read and write from HDFS. So this is the directory which I've created, which will contain my output once the MapReduce job finishes. And this is my cluster file system. If you look on this UI, this shows me about my yarn, which is available for taking care of any processing. It as of now shows that I have total of 8 GB memory and I have 8 vCores. Now that can be depending on what configuration we have set or how many nodes are available. We can look at nodes which are available, and that shows me I have 2 node managers running. Each has 8 GB memory and 8 vCores. Now that's not true actually, but then we have not set the configurations for node managers, and that's why it takes the default properties, that is 8 GB RAM and 8 vCores. Now this is my yarn UI. We can also look at scheduler, which basically shows me the different queues if they have been configured, where you will have to run the jobs. We'll discuss about all these later in detail. Now let's go back to our terminal and let's see where we can find some sample applications which we can run on the cluster. So once I go to the terminal, I can, well, submit the MapReduce job from any terminal. Now here I know that my Hadoop related directory is here, and within Hadoop you have various directories. We have discussed that in binaries you have the commands which you can run. In sbin you basically have the startup scripts, and here you also notice there is a share directory in the end. If you look in the share directory, you would find Hadoop, and within Hadoop you have various subdirectories in which we will look for MapReduce. Now this MapReduce directory has some sample jar files which we can use to run a MapReduce on the cluster. Similarly, if you are working on a Cloudera cluster, you would have to go into opt Cloudera parcel cdh/lib, and in that you would have directories for HDFS MapReduce or HDFS yarn, where you can still find the same jars. It is basically a package which contains your multiple applications. Now how do we run a MapReduce? We can just type in Hadoop and hit enter, and that shows me that I have an option called jar, which can be used to run a jar file. Now at any point of time, if you would want to see what are the different classes which are available in a particular jar, you could always do a jar -xvf. For example, I could say jar xvf, and I could say user local Hadoop share Hadoop MapReduce, and then list down your jar file. So I'll say Hadoop MapReduce examples, and if I do this, this should basically unpack it to show me what classes are available within this particular jar. And it has done this. It has created a meta file and it has created a org directory. We can see that by doing a ls, and here if you look in ls org, since I ran the command from a home directory, I can look into org Apache Hadoop examples, which shows me the classes which I have, and those classes contain which mapper or reducer classes. So it might not be just mapper and reducer, but you can always have a look. So for example, I am targeting to use word count program, which does a word count on files and gives me a list of words and how many times they occur in a particular file or in set of files. And this shows me that what are the classes which belong to word count. So we have a int sum reducer. So this is my reducer class. I have tokenizer mapper, that is my mapper class, right? And basically this is what is used. These classes are used if you run a word count. Now there are many other programs which are part of this jar file, and we can expand and see that. So I can say Hadoop jar and give your path. So I'll say Hadoop jar user local Hadoop share Hadoop MapReduce examples, and if I hit on enter, that will show me what are the inbuilt classes which are already available. Now these are certain things which we can use. Now there are other jar files also. For example, I can look at Hadoop, and here we can look at the jar files which we have in this particular path. So this is one Hadoop MapReduce examples which you can use. You can always look in other jar files, like you can look for Hadoop MapReduce client, job client, and then you can look at the tests one. So that is also an interesting one. So you can always look into Hadoop, MapReduce, client, job client, and then you have something ending with tests. So if I would have tried this one using my Hadoop jar command, so in my previous example, when we did this, it was showing me all the classes which are available, and that already has a word count. Now there are other good programs which you can try, like TerraGen to generate dummy data, TerraSort to check your sorting performance, and so on, and TerraValidate to validate the results. Similarly, we can also do a Hadoop jar, as I said, on Hadoop MapReduce. I think that was client, and then we have job client, and then test jar. Now this has a lot of other classes which can be used, or programs which can be used for doing a stress testing or checking your cluster status and so on. One of them, interesting one, is test HDFS. But let's not get into all the details in first instance. Let's see how we can run a MapReduce. Now if I would want to run a MapReduce, I need to give Hadoop jar and then my jar file, and if I hit on enter, it would say it needs the input and output. It needs which class you want to run. So for example, I would say word count, and again if I hit on enter, it tells me that you need to give me some input and output to process. And obviously this processing will be happening on cluster, that is our yarn processing framework, unless and until you would want to run this job in a local mode. So there is a possibility that you can run the job in a local mode, but let's first try how it runs on the cluster. So how do we do that? Now here I can do a HDFS ls / command to see what I have on my HDFS. Now through my UI, I was already showing you that we have set of files and directories which we can use to process. Now we can take up one single file. So for example, if I pick up new data, and I can look into the files here, what we have, and we can basically run a MapReduce on a single file or multiple files. So let's take this file, whatever that contains, and I would like to do a word count so that I get a list of words and their occurrence in this file. So let me just copy this. Now I also need my output to be written, and that will be written here. So here, if I want to run a MapReduce, I can say Hadoop, which we can pull out from history. So Hadoop jar word count. Now I need to give my input, so that will be new data, and then I will give this file which we just copied. Now I'm going to run the word count only on a single file, and I will basically have my output which will be stored in this directory, the directory which I have created already, mr output. So let's do this output, and this is fair enough. Now you can give many other properties. You can specify how many map jobs you want to run, how many reduce jobs you want to run. Do you want your output to be compressed? Do you want your output to be merged? Or many other properties can be defined when you are specifying word count, and then you can pass in an argument to pass properties from the command line which will affect your output. Now once I go ahead and submit this, this is basically running a simple inbuilt MapReduce job on our Hadoop cluster. Now obviously internally it will be looking for name node. Now we have some issue here, and it says the output already exists. What does that mean? So it basically means that Hadoop will create an output for you. You just need to give a name, but then you don't need to create it. So let's append the output with number 1, and then let's go ahead and run this. So I've submitted this command. Now this can also be run in background if you would want to run multiple jobs on your cluster at the same time. So it takes total input paths to process is 1. So that is, there is only one split on which your job has to work. Now it will internally try to contact your resource manager, and basically this is done. So here we can have a look, and we can see some counters here. Now what I also see is for some property which it is missing, it has run the job, but it has run in a local mode. It has run in a local mode. So although we have submitted, so this might be related to my yarn settings, and we can check that. So if I do a refresh, when I have run my application, it has completed. It would have created an output, but the only thing is it did not interact with your yarn. it did not interact with your resource manager. We can check those properties, and here if we look into the job, it basically tells me that it went for mapping and reducing. It would have created an output, it worked on my file, but then it ran in a local mode. So MapReduce, remember, is a programming model, right? Now, if you run it on Yarn, you get the facilities of running it on a cluster where Yarn takes care of resource management. If you don't run it on Yarn and run it on a local mode, it will use your machine's RAM and CPU cores for processing. But then we can quickly look at the output, and then we can also try running this on Yarn. So if I look into my HDFS and if I look into my output, MR output, that's the directory which was not used actually. Let's look into the other directory which is ending with 1, and that should show me the output created by this MapReduce. Although it ran in a local mode, it fetched an input file from your HDFS and it would have created output in HDFS. Now that's my part file which is created, and if you look at part minus R minus these zeros, if you would have more than one reducer running, then you would have multiple such files created. We can look into this. What does this file contain? Which should have my word count, and here I can say cat, which basically shows me what is the output created by my MapReduce. Let's have a look into this. So the file which we gave for processing has been broken down, and now we have the list of words which occur in the file plus a count of those words. So if there is some word which is more, then it shows me the count. So this is a list of my words and the count for that. So this is how we run a sample MapReduce job. I will also show you how we can run it on Yarn. Now let's run MapReduce on Yarn, and initially when we tried running a MapReduce, it did not hit Yarn, but it ran in a local mode, and that was because there was a property which had to be changed in MapReduce-site file. So basically, if you look into this file, the error was that I had given a property which says mapred.framework.name, and that was not the right property name, and it was ignored, and that's why it ran in a local mode. So I changed the property to mapReduce.framework.name, restarted my cluster, and everything should be fine now. And that mapred-site file has also been copied across the nodes. Now to run a MapReduce on a Hadoop cluster so that it uses Yarn, and Yarn takes care of resource allocation on one or multiple machines. So I'm just changing the output here, and now I will submit this job, which should first connect to the resource manager. And if it connects to the resource manager, that means our job will be run using Yarn on the cluster rather than in a local mode. So now we have to wait for this application to internally connect to resource manager, and once it starts there, we can always go back to the web UI and check if our application has reached Yarn. So it shows me that there is one input part to be processed. That's my job ID, that's my application ID, which you can even monitor status from the command line. Now here the job has been submitted. So let's go back here and just do a refresh on my Yarn UI, which should show me the new application which is submitted. It tells me that it is in accepted state. Application master has already started, and if you click on this link, it will also give you more details of how many map and reduce tasks would run. So as of now, it says the application master is running. It would be using this node which is M1. We can always look into the logs. We can see that there is a one task attempt which is being made. And now if I go back to my terminal, I will see that it is waiting to get some resources from the cluster. And once it gets the resources, it will first start with the mapping phase, where the mapper function runs. It does the map tasks, one or multiple depending on the splits. So right now we have one file and one split, so we will have just one map task running. And once the mapping phase completes, then it will get into reducing, which will finally give me my output. So we can be toggling through these sessions. So here I can just do a refresh to see what is happening with my application. Is it proceeding? Is it still waiting for resource manager to allocate some resources? Now, just a couple of minutes back, I tested this application on Yarn, and we can see that my first application completed successfully. And here we will have to give some time so that Yarn can allocate the resources. Now, if the resources were used by some other application, they will have to be freed up. Now, internally, Yarn takes care of all that, which we will learn more detail in Yarn, or you might have already followed the Yarn based session. Now here we will have to just give it some more time, and let's see if my application proceeds with the resources what Yarn can allocate to it. Sometimes you can also see a slowness in what web UI shows up, and that can be related to the amount of memory you have allocated to your nodes. Now for Apache, we can have less amount of memory and we can still run the cluster. And as I said, the memory which shows up here, 16 GB and 16 cores, is not the true one. Those are the default settings, right? But then my Yarn should be able to facilitate running of this application. Let's just give it a couple of seconds and then let's look into the output here. Again, I had to make some changes in the settings because our application was not getting enough resources, and then basically I restarted my cluster. Now let's submit the application again to the cluster, which first should contact the resource manager, and then basically the map and reduce process should start. So here I've submitted an application. It is connecting to the resource manager, and then basically it will start internally an app master, that is application master. It is looking for the number of splits, which is 1. It's getting the application ID, and it basically then starts running the job. It also gives you a tracking URL to look at the output. And now we should go back and look at our Yarn UI if our application shows up here, and we will have to give it a couple of seconds when it can get the final status change to running, and that's where my application will be getting resources. Now if you closely notice here, I have allocated specific amount of memory, that is 1.5 GB for node manager on every node, and I have basically given 2 cores each, which my machines also have, and my Yarn should be utilizing these resources rather than going for default. Now the application has started moving, and we can see the progress bar here, which basically will show what is happening. And if we go back to the terminal, it will show that first it went in deciding map and reduce. It goes for map. Once the mapping phase completes, then the reducing phase will come into existence, and here my job has completed. So now it has basically used, we can always look at how many map and reduce tasks were run. It shows me that there was 1 map and 1 reduce task. Now with the number of map tasks depends on the number of splits, and we had just 1 file which is less than 128 MB, so that was 1 split to be processed, and reduce task is internally decided by the reducer, or depending on what kind of property has been set in Hadoop config files. Now it also tells me how many input records were read, which basically means these were the number of lines in the file. It tells me output records, which gives me the number of total words in the file. Now there might be duplicates, and that which is processed by internal combiner, further processing or forwarding that information to reducer, and basically reducer works on 335 records, gives us a list of words and their count. Now if I do a refresh here, this would obviously show my application is completed. It says succeeded. You can always click on the application to look for more information. It tells me where it ran. Now we do not have a history server running as of now, otherwise we can always access more information. So this leads to history server where all your applications are stored. But I can click on this attempt tasks, and this will basically show me the history URL, or you can always look into the logs. So this is how you can submit a sample application which is inbuilt, which is available in the jar on your Hadoop cluster, and that will utilize your cluster to run. Now you could always, as I said, when you're running a particular job, remember to change the output directory, and if you would not want it to be processing a single individual file, you could also point it to a directory. That basically means it will have multiple files, and depending on the file sizes, there would be multiple splits, and according to that, multiple map tasks will be selected. So if I click on this, this would submit my second application to the cluster, which should first connect to resource manager. Then resource manager has to start an application master. Now here we are targeting 10 splits. Now you have to sometimes give a couple of seconds in your machines so that the resources which were used are internally already freed up, so that your cluster can pick it up, and then your Yarn can take care of resources. So right now my application is in undefined status, but then as soon as my Yarn provides it the resources, we will have the application running on our yarn cluster. So it has already started. If you see, it is going further. Then it would launch 10 map tasks, and the number of reduced tasks would be decided on either the way your data is or based on the properties which have been set at your cluster level. Let's just do a quick refresh here on my yarn UI to show me the progress. Also take care that when you are submitting your application, you need to have the output directory mentioned. However, do not create it. Hadoop will create that for you. Now, this is how you run a MapReduce without specifying properties, but then you can specify more properties. You can look into what are the things which can be changed for your mapper and reducer, or basically having a combiner class which can do a mini reducing, and all those things can be done. So we will learn about that in the later sessions. Now we will compare Hadoop version 1, that is with MapReduce version 1. We will understand and learn about the limitations of Hadoop version 1. What is the need of yarn? What is yarn? What kind of workloads can be running on yarn? What are yarn components? What is yarn architecture? And finally, we will see a demo on yarn. So Hadoop version 1 or MapReduce version 1. Well, that's outdated now, and nobody is using Hadoop version 1, but it would be good to understand what was in Hadoop version 1 and what were the limitations of Hadoop version 1, which brought in the thought for the future processing layer, that is yarn. Now, when we talk about Hadoop, we already know that Hadoop is a framework, and Hadoop has two layers. One is your storage layer, that is your HDFS, Hadoop Distributed File System, which allows for distributed storage and processing, which allows fault tolerance by inbuilt replication, and which basically allows you to store huge amount of data across multiple commodity machines. When we talk about processing, we know that MapReduce is the oldest and the most mature processing programming model, which basically takes care of your data processing on your distributed file system. So in Hadoop version 1, MapReduce performed both data processing and resource management, and that's how it was problematic. In MapReduce, we had basically, when we talk about the processing layer, we had the master, which was called job tracker, and then you had the slaves, which were the task trackers. So your job tracker was taking care of allocating resources, it was performing scheduling, and even monitoring the jobs. It basically was taking care of assigning map and reduce tasks to the jobs running on task trackers, and task trackers, which were co-located with data nodes, were responsible for processing the jobs. So task trackers were the slaves for the processing layer, which reported their progress to the job tracker. So this is what was happening in Hadoop version 1. Now, when we talk about Hadoop version 1, we would have, say, client machines or an API or an application which basically submits the job to the master, that is job tracker. Now, obviously, we cannot forget that there would already be an involvement from name node, which basically tells which are the machines or which are the data nodes where the data is already stored. Now, once the job submission happens to the job tracker being the master daemon for taking care of your processing request and also resource management, job scheduling, would then be interacting with your multiple task trackers, which would be running on multiple machines. So each machine would have a task tracker running, and that task tracker, which is a processing slave, would be co-located with the data nodes. Now we know that in case of Hadoop, you have the concept of moving the processing to wherever the data is stored rather than moving the data to the processing layer. So we would have task trackers which would be running on multiple machines, and these task trackers would be responsible for handling the tasks. What are these tasks? These are the application which is broken down into smaller tasks which would work on the data which is respectively stored on that particular node. Now these were your slave daemons, right? So your job tracker was not only tracking the resources, so your task trackers were sending heartbeats, they were sending in packets and information to the job tracker, which would then be knowing how many resources. And when we talk about resources, we are talking about the CPU cores, we are talking about the RAM which would be available on every node. So task trackers would be sending in their resource information to job tracker, and your job tracker would be already aware of what amount of resources are available on a particular node, how loaded a particular node is, what kind of work could be given to the task tracker. So job tracker was taking care of resource management, and it was also breaking the application into tasks and doing the job scheduling part, assign different tasks to these slave daemons, that is your task trackers. So job tracker was eventually overburdened, right? Because it was managing jobs, it was tracking the resources from multiple task trackers, and basically it was taking care of job scheduling. So job tracker would be overburdened, and in a case if job tracker would fail, then it would affect the overall processing. So if the master is killed, if the master daemon dies, then the processing cannot proceed. Now this was one of the limitations of Hadoop version 1. So when you talk about scalability, that is the capability to scale, due to a single job tracker, scalability would be hitting a bottleneck. You cannot have a cluster size of more than 4,000 nodes and cannot run more than 40,000 concurrent tasks. Now that's just a number. We could always look into the individual resources which each machine was having, and then we can come up with an appropriate number. However, with a single job tracker, there was no horizontal scalability for the processing layer because we had single processing master. Now when we talk about availability, job tracker, as I mentioned, would be a single point of failure. Now any failure kills all the queued and running jobs, and jobs would have to be resubmitted. Now why would we want that? In a distributed platform, in a cluster which has hundreds and thousands of machines, we would want a processing layer which can handle huge amount of processing, which could be more scalable, which could be more available, and could handle different kind of workloads. When it comes to resource utilization, now if you would have a predefined number of map and reduce slots for each task tracker, you would have issues which would relate to resource utilization, and that again is putting a burden on the master which is tracking these resources, which has to assign jobs which can run on multiple machines in parallel. So limitations in running non-MapReduce applications. Now that was one more limitation of Hadoop version 1 and MapReduce, that the only kind of processing you could do is MapReduce. And MapReduce programming model, although it is good, it is oldest, it has matured over a period of time, but then it is very rigid. You will have to go for mapping and reducing approach. And that was the only kind of processing which could be done in Hadoop version 1. So when it comes to doing a real-time analysis, or doing ad hoc query, or doing a graph-based processing or massive parallel processing, there were limitations because that could not be done in Hadoop version 1, which was having MapReduce version 1 as the processing component. Now that brings us to the need for YARN. So YARN, it stands for yet another resource negotiator. So as I mentioned before, YARN in Hadoop version 1, well, you could have applications which could be written in different programming languages, but then the only kind of processing which was possible was MapReduce. We had the storage layer, we had the processing, but then kind of limited processing which could be done. Now, this was one thing which brought in a thought that why shouldn't we have a processing layer which can handle different kind of workloads? As I mentioned, might be graph processing, might be real-time processing, might be massive parallel processing, or any other kind of processing which would be a requirement of an organization. Now, designed to run MapReduce jobs only and having issues in scalability, resource utilization, job tracking, etc., that led to the need of something what we call as YARN. Now from Hadoop version 2 onwards, we have the two main layers have changed a little bit. You have the storage layer which is intact, that is your HDFS, and then you have the processing layer which is called YARN, yet another resource negotiator. Now we will understand how YARN works, but then YARN is taking care of your processing layer. It does support MapReduce, so MapReduce processing can still be done, but then now you can have a support to other processing frameworks. YARN can be used to solve the issues which Hadoop version 1 was posing. Something like resource management, something like different kind of workload processing, something like scalability, resource utilization, all that is now taken care by YARN. Now, when we talk about Yarn, we can have now a cluster size of more than 10,000 nodes and can run more than 100,000 concurrent tasks. That's just to take care of your scalability. When you talk about compatibility, applications which were developed for Hadoop version 1, which were primarily MapReduce kind of processing, can run on Yarn without any disruption or availability issues. When you talk about resource utilization, there is a mechanism which takes care of dynamic allocation of cluster resources. And this basically improves the resource utilization. When we talk about multi-tenancy, so basically now the cluster can handle different kind of workloads. So you can use open source and proprietary data access engines. You can perform real-time analysis. You can be doing graph processing. You can be doing ad hoc querying. And this can be supported for multiple workloads which can run in parallel. So this is what Yarn offers. So what is Yarn? As I mentioned, Yarn stands for yet another resource negotiator. So it is the cluster resource management layer for your Apache Hadoop ecosystem, which takes care of scheduling jobs and assigning resources. Now, just imagine when you would want to run a particular application, you would basically be telling the cluster that I would want resources to run my applications. That application might be a MapReduce application. That might be a Hive query, which is triggering a MapReduce. That might be a pig script, which is triggering a MapReduce. That could be Hive with Daze as an execution engine. That could be a Spark application. That could be a graph processing application. In any of these cases, you would still, you as in sense client or basically an API or the application would be requesting for resources. Yarn would take care of that. So Yarn would provide the desired resources. Now when we talk about resources, we are mainly talking about the network related resources. We are talking about the CPU cores, or as in terms of Yarn we say virtual CPU cores. We would talk about RAM, that is in GB or MB or in terabytes, which would be offered from multiple machines, and Yarn would take care of this. So with Yarn, you could basically handle different workloads. Now these are some of the workloads which are showing up here. You have the traditional MapReduce, which is mainly batch oriented. You could have an interactive execution engine, something as Daze. You could have HBase, which is a column oriented or a 4-dimensional database, and that would be not only storing data on HDFS but would also need some kind of processing. You could have streaming functionalities, which would be from Storm or Kafka or Spark. You could have graph processing. You could have in-memory processing such as Spark and its components, and you could have many others. So these are different frameworks which could now run and which can run on top of Yarn. So how does Yarn do that? Now when we talk about Yarn, this is how a overall Yarn architecture looks. So at one end you have the client. Now client could be basically your edge node where you have some applications which are running. It could be an API which would want to interact with your cluster. It could be a user triggered application which wants to run some jobs which are doing some processing. So this client would submit a job request. Now what is Resource Manager doing? Resource Manager is the master of your processing layer. In Hadoop version 1, we basically had job tracker, and then we had task trackers which were running on individual nodes. So your task trackers were sending your heartbeats to the job tracker. Your task trackers were sending it their resource information, and job tracker was the one which was tracking the resources and it was doing the job scheduling. And that's how, as I mentioned earlier, job tracker was overburdened. So job tracker is now replaced by your resource manager, which is the master for your processing layer. Your task trackers are replaced by node managers, which would be then running on every node. And we have a temporary daemon, which you see here in blue, and that's your app master. So this is what we mention when we say yet another resource negotiator. So app master would be existing in a Hadoop version 2. Now, when we talk about your resource manager is the master for processing layer. So it would already be receiving heartbeats, and you can say resource information from multiple node managers, which would be running on one or multiple machines. And these node managers are not only updating their status, but they are also giving an information of the amount of resources they have. Now, when we talk about resources, we should understand that if I'm talking about this node manager, then this has been allocated some amount of RAM for processing and some amount of CPU cores. And that is just a portion of what the complete node has. So if my node has, say, imagine my node has around 100 GB RAM and I have, say, 60 cores, all of that cannot be allocated to node manager. So node manager is just one of the components of Hadoop ecosystem. It is the slave of the processing layer. So we could say, keeping in all the aspects, such as different services which are running, might be Cloudera or Hortonworks related services running, system processes running on a particular node, some portion of this would be assigned to node manager for processing. So we could say, for example, say 60 GB RAM per node and say 40 CPU cores. So this is what is allocated for the node manager on every machine. Similarly, we would have here. Similarly, we would have here. So node manager is constantly giving an update to resource manager about the resources, what it has. Probably there might be some other applications running and node manager is already occupied. So it gives an update. Now we also have a concept of containers, which is basically we will talk about, which is about these resources being broken down into smaller parts. So resource manager is keeping a track of the resources which every node manager has, and it is also responsible for taking care of the job request. How do these things happen? Now, as we see here, resource manager at a higher level, you can always say this is the processing master which does everything. But in reality, it is not the resource manager which is doing it, but it has internally different services or components which are helping it to do what it is supposed to do. Now let's look further. Now, as I mentioned, your resource manager has these services or components which basically helps it to do the things. It is basically an architecture where multiple components are working together to achieve what Yarn allows. So resource manager has mainly two components, that is your scheduler and applications manager, and these are at high level four main components here. So we talk about resource manager, which is the processing master. You have node managers, which are the processing slaves which are running on every nodes. You have the concept of container, and you have the concept of application master. How do all these things work? Now let's look at Yarn components. So resource manager basically has two main components, you can say, which assist resource manager in doing what it is capable of. So you have scheduler and applications manager. Now there is, when you talk about resources, there is always a requirement for the applications which need to run on cluster of resources. So your application which has to run, which was submitted by client, needs resources, and these resources are coming in from multiple machines wherever the relevant data is stored and a node manager is running. So we always know that node manager is co-located with data nodes. Now, what does the scheduler do? So we have different kind of schedulers here. We have basically a capacity scheduler, we have a fair scheduler, or we could have a FIFO scheduler. So there are different schedulers which take care of resource allocation. So your scheduler is responsible for allocating resources to various running applications. Now imagine a particular environment where you have different teams or different departments which are working on the same cluster. So we would call the cluster as a multi-tenant cluster. And on the multi-tenant cluster, you would have different applications which would want to run simultaneously accessing the resources of the cluster. How is that managed? So there has to be some component which has a concept of pooling or queuing so that different departments or different users can get dedicated resources or can share resources on the cluster. So scheduler is responsible for allocating resources to various running applications. Now it does not perform monitoring or tracking of the status of applications. That's not the part of scheduler. It does not offer any guarantee about restarting the failed tasks due to hardware or network or any other failures. Scheduler is mainly responsible for allocating resources. Now, as I mentioned, you could have different kind of schedulers. You could have a FIFO scheduler, which was mainly in older version of Hadoop, which stands for first in, first out. You could have a fair scheduler, which basically means multiple applications could be running in the cluster and they would have a fair share of the resources. You could have a capacity scheduler, which would basically have dedicated or fixed amount of resources across the cluster. Now, whichever scheduler is being used, scheduler is mainly responsible for allocating resources. Then it's your applications manager. Now, this is responsible for accepting job submissions. Now, as I said, at higher level, we could always say resource manager is doing everything. It is allocating the resources, it is negotiating the resources, it is also taking care of listening to the clients and taking care of job submissions. But who is doing it in real? It is these components. So you have applications manager, which is responsible for accepting job submissions. It negotiates the first container for executing the application specific application master. It provides the service for restarting the application master. Now, how does this work? How do these things happen in coordination? Now, as I said, your node manager is the slave process which would be running on every machine. Slave is tracking the resources, what it has. It is tracking the processes. It is taking care of running the jobs. And basically, it is tracking each container resource utilization. So let's understand what is this container. So normally when you talk about an application request which comes from a client, so let's say this is my client which is requesting or which is coming up with an application which needs to run on the cluster. Now this application could be anything. It first contacts your master. That's your resource manager, which is the master for your processing layer. Now, as I mentioned, and as we already know, that your name node, which is the master of your cluster, has the metadata in its RAM, which is aware of the data being split into blocks, the blocks when stored on multiple machines, and other information. So obviously there was a interaction with the master which has given this information of the relevant nodes where the data exists. Now for the processing need, your client, basically the application which needs to run on the cluster. So your resource manager, which basically has the scheduler which takes care of allocating resources, and a resource manager has mainly these two components which are helping it to do its work. Now for a particular application which might be needing data from multiple machines. Now we know that we would have multiple machines where we would have node manager running, we would have a data node running, and data nodes are responsible for storing the data on disk. So your resource manager has to negotiate the resources. Now when I say negotiating the resources, it could basically ask each of these node managers for some amount of resources. For example, it would be saying, can I have 1 GB of RAM and 1 CPU core from you? Because there is some data residing on your machine and that needs to be processed as part of my application. Can I again have 1 GB and 1 CPU core from you? And this is again because some relevant data is stored. And this request which resource manager makes of holding the resources of total resources which the node manager has, your resource manager is negotiating or is asking for resources from the processing slave. So this request of holding resources can be considered as a container. So resource manager, now we know it is not actually the resource manager, but it is the application manager which is negotiating the resources. So it negotiates the resources which are called container. So this request of holding resource can be considered as a container. So basically a container can be of different sizes. We will talk about that. So resource manager negotiates the resources with node manager. Now node manager, which is already giving an update of the resources it has, what amount of resources it holds, how much busy it is, can basically approve or deny this request. So node manager would basically approve in saying, yes, I could hold these resources. I could give you this container of this particular size. Now once the container has been approved or allocated, or you can say granted by your node manager, resource manager now knows that resources to process the application are available and guaranteed by the node manager. So resource manager starts a temporary daemon called app master. So this is a piece of code which would also be running in one of the containers. It would be running in one of the containers, which would then take care of execution of tasks in other containers. So your application master is per application. So if I would have 10 different applications coming in from the client, then we would have 10 app masters, one app master being responsible for per application. Now what does this app master do? It basically is a piece of code which is responsible for execution of the application. So your app master would run in one of the containers, and then it would use the other containers which node manager is guaranteed that it will give when the application request comes to it, and using these containers the app master will run the processing tasks within these designated resources. So it is mainly the responsibility of application master to get the execution done and then communicate it to the master. So resource manager is tracking the resources, it is negotiating the resources, and once the resources have been negotiated, it basically gives the control to application master. Application master is then running within one of the containers on one of the nodes and using the other containers to take care of execution. This is how it looks. So basically, container, as I said, is a collection of resources like CPU, memory, your disk, which would be used or which already has the data, and network. So your node manager is basically looking into the request from application master, and it basically is granting this request or basically is allocating these containers. Now again, we could have different sizing of the containers. Let's take an example here. So as I mentioned, from the total resources which are available for a particular node, some portion of resources are allocated to the node manager. So let's imagine this is my node where node manager as a processing slave is running. So from the total resources which the node has, some portion of RAM and CPU cores is basically allocated to the node manager. So I could say out of total 100 GB RAM, we can say around 60 cores which the particular node has. So this is my RAM which the node has, and these are the CPU cores which the node has, some portion of it, right? So we can say might be 70% or 60% of the total resources. So we could say around 60 GB RAM, and then we could say around 40 vcores have been allocated to node manager. So there are these settings which are given in the yarn-site file. Now, apart from this allocation, that is 60 GB RAM and 40 vcores, we also have some properties which say what will be the container sizes. So for example, we could have a small container setting which could say my every container could have 2 GB RAM and say 1 virtual CPU core. So this is my smallest container. So based on the total resources, you could calculate how many such small containers could be running. So if I say 2 GB RAM, then I could have around 30 containers. But then I'm talking about one virtual CPU core. So totally I could have around 30 small containers which could be running in parallel on a particular node. And as of that calculation, you would say 10 CPU cores are not being utilized. You could have a bigger container size which could say I would go for 2 CPU cores and 3 GB RAM. So 3 GB RAM and 2 CPU cores. So that would give me around 20 containers of bigger size. So this is the container sizing, which is again defined in the yarn-site file. So what we know is on a particular node which has this kind of allocation, either we could have 30 small containers running or we could have 20 big containers running, and same would apply to multiple nodes. So node manager, based on the request from application master, can allocate these containers. Now remember, it is within this one of these containers you would have an application master running, and other containers could be used for your processing requirement. Application master, which is per application, it is the one which uses these resources. It basically manages or uses these resources for individual application. So remember, if we have 10 applications running on Yarn, then it would be 10 application masters, one responsible for each application. Your application master is the one which also interacts with the scheduler to basically know how much amount of resources could be allocated for one application. And your application master is the one which uses these resources, but it can never negotiate for more resources to node manager. Application master cannot do that. Application master has to always go back to resource manager if it needs more resources. So it is always the resource manager, and internally resource manager's component, that is application manager, which negotiates the resources. At any point of time, due to some node failures or due to any other requirements, if application master needs more resources on one or multiple nodes, it will always be contacting the resource manager, internally the applications manager, for more containers. Now this is how it looks. So your client submits the job request to resource manager. Now we know that resource manager internally has scheduler and applications manager. Node managers which are running on multiple machines are the ones which are tracking their resources, giving this information to resource manager so that resource manager, or I would say its component applications manager, could request resources from multiple node managers. When I say request resources, it is these containers. So your resource manager basically will request for the resources on one or multiple nodes. Node manager is the one which approves these containers, and once the container has been approved, your resource manager triggers a piece of code, that is application master, which obviously needs some resources, so it would run in one of the containers and will use other containers to do the execution. So your client submits an application to resource manager. Resource manager allocates a container, or I would say this is at a high level, right? Resource manager is negotiating the resources, and internally who is negotiating the resources? It is your applications manager. Who is granting this request? It is node manager. And that's how we can say resource manager allocates a container. Application master basically contacts the related node manager because it needs to use the containers. Node manager is the one which launches the container, or basically gives those resources within which an application can run. And application master itself will then accommodate itself in one of the containers and then use other containers for the processing. And it is within these containers the actual execution happens. Now that could be a map task, that could be a reduce task, that could be a Spark executor taking care of Spark tasks, and many other processing. So before we look into the demo on how Yarn works, I would suggest looking into one of the blogs from Cloudera. So you can just look for Yarn untangling, and this is really a good blog which basically talks about the overall functionality which I explained just now. So as we mentioned here, so you basically have the master process, you have the worker process which basically takes care of your processing, your resource manager being the master, and node manager being the slave. This also talks about the resources which each node manager has. It talks about the Yarn configuration file where you give all these properties. It basically shows you node manager which reports the amount of resources it has to resource manager. Now remember, if worker node shows 8 into 8 CPU cores and 128 GB RAM, and if your node manager says 64 vCores and RAM 128 GB, then that's not the total capacity of your node. It is some portion of your node which is allocated to node manager. Now once your node manager reports that, your resource manager is requesting for containers based on the application. What is a container? It is basically a logical name given to a combination of vCore and RAM. It is within this container where you would have basically the process running. So once your application starts and once node manager is guaranteed these containers, your application or your resource manager has basically already started an application master within the container. And what does that application master do? It uses the other containers where the tasks would run. So this is a very good blog which you can refer to, and this also talks about MapReduce. If you have already followed the MapReduce tutorials in past, then you would know about the different kind of tasks, that is map and reduce, and these map and reduce tasks could be running within the container in one or multiple. As I said, it could be map task, it could be reduce task, it could be a Spark based task which would be running within the container. Now once the task finishes, basically that resources can be freed up. So the container is released and the resources are given back to Yarn so that it can take care of further processing. If you'll further look in this blog, you can also look into the part 2 of it where you talk mainly about configuration settings. You can always look into this, which talks about why and how much resources are allocated to the node manager. It basically talks about your operating system overhead. It talks about other services. It talks about Cloudera or Hortonworks related services running and other processes which might be running. And based on that, some portion of RAM and CPU cores would be allocated to node manager. So that's how it would be done in the yarn-site file, and this basically shows you what is the total amount of memory and CPU cores which is allocated to node manager. Then within every machine where you have a node manager running, on every machine in the yarn-site file, you would have such properties which would say what is the minimum container size, what is the maximum container size. In terms of RAM, what is the minimum for CPU cores, what is the maximum for CPU cores, and what is the incremental size in where RAM and CPU cores can increment. So these are some of the properties which define how containers are allocated for your application request. So have a look at this, and this could be a good information which talks about different properties. Now you can look further, which talks about scheduling. If you look in this particular blog, which also talks about scheduling, where it talks about scheduling in Yarn, which talks about fair scheduler, or you basically having different queues in which allocations can be done. You also have different ways in which queues can be managed and different schedulers can be used. So you can always look at this series of blog. You can also be checking for Yarn schedulers and then search for Hadoop definitive guide, and that could give you some information on how it looks when you look for Hadoop definitive guide. So if you look into this book, which talks about the different resources, as I mentioned, so you could have a FIFO scheduler, that is first in first out, which basically means if a long running application is submitted to the cluster, all other small running applications will have to wait. There is no other way, but that would not be a preferred option if you look in FIFO scheduler. If you look for capacity scheduler, it basically means that you could have different queues created and those queues would have resources allocated. So then you could have a production queue where production jobs are running in a particular queue which has fixed amount of resources allocated. You could have a development queue where development jobs are running and both of them are running in parallel. You could then also look into fair scheduler, which basically means again multiple applications could be running on the cluster, however they would have a fair share. So when I say fair share, in brief, what it means is if I had given 50% of resources to a queue for production and 50% of resources for a queue of development, and if both of them are running in parallel, then they would have access to 50% of cluster resources. However, if one of the queue is unutilized, then second queue can utilize all cluster resources. So look into the fair scheduling part. It also shows you about how allocations can be given, and you can learn more about schedulers and how queues can be used for managing multiple applications. Now we will spend some time in looking into few ways or few quick ways in interacting with Yarn in the form of a demo. To understand and learn on how Yarn works, we can look into a particular cluster. Now here we have a designated cluster which can be used. You could be using the similar kind of commands on your Apache based cluster or a Cloudera Quick Start VM if you already have, or if you have a Cloudera or a Hortonworks cluster running. There are different ways in which we can interact with Yarn and we can look at the information. One is basically looking into the admin console. So if I would look into Cloudera Manager, which is basically an admin console for a Cloudera's distribution of Hadoop. Similarly, you could have a Hortonworks cluster and access to the admin console. So if you have even read access for your cluster, and if you have the admin console, then you can search for Yarn as a service which is running. You can click on Yarn as a service, and that gives you different tabs. So you have the instances, which tells basically what are the different roles for your Yarn service running. So we have here multiple node managers. Now some of them show in stop status, but that's nothing to worry. So we have 3 and 6 node managers. We have resource manager, which is 1, but then that can also be in a high availability where you can have active and standby. You also have a job history server which would show you the applications once they have completed. Now you can look at the Yarn configurations, and as I was explaining, you can always look for the properties which are related to the allocation. So you can here search for course, and that should show you the properties which talk about the allocations. So here if we see, we can be looking for Yarn app MapReduce application master resource CPU cores. What is the CPU cores allocated for MapReduce, map task, reduce task? You can be looking at Yarn node manager resource CPU cores, which basically says every node manager on every node would be allocated with 6 CPU cores, and the container sizing is with minimum allocation of 1 CPU core and the maximum could be 2 CPU cores. Similarly, you could also be searching for memory allocation, and here you could then scroll down to see what kind of memory allocation has been done for the node manager. So if we look further, it should give me information of node manager, which basically says here that the container minimum allocation is 2 GB, the maximum is 3 GB, and we can look at node manager which has been given 25 GB per node. So it's a combination of this memory and CPU cores, which is the total amount of resources which have been allocated to every node manager. Now we can always look into applications tab that would show us different applications which are submitted on Yarn. For example, right now we see there is a Spark application running, which is basically a user who is using Spark shell, which has triggered a application on Spark, and that is running on Yarn. You can look at different applications, workload information. You can always do a search based on the number of days, how many applications have run, and so on. You can always go to the web UI and you can be searching for the resource manager web UI, and if you have access to that, it will give you overall information of your cluster. So this basically says that here we have 100 GB memory allocated, so that could be say 25 GB per node, and if we have 4 node managers running and we have 24 cores, which is 6 cores per node. If we look further here into nodes, I could get more information. So this tells me that I have 4 node managers running, and node managers basically have 25 GB memory allocated per node and 6 cores, out of which some portion is being utilized. We can always look at the scheduler here, which can give us information what kind of scheduler has been allocated. So we basically see that there is just a root queue, and within root you have default queue and you have basically users queue based on different users. We can always scroll here, and that can give us information if it is a fair share. So here we see that my root.default has 50% of resources, and the other queue also has 50% of resources, which also gives me an idea that a fair scheduler is being used. We can always confirm that if we are using a fair scheduler or a capacity scheduler which takes care of allocations. So search for scheduler, and that should give you some understanding of what kind of scheduler is being used and what are the allocations given for that particular scheduler. So here we have fair scheduler. It shows me you have under root, you have the root queue which has been given 100% capacity, and then you have within that default which also takes 100%. So this is how you can understand about Yarn by looking into the Yarn web UI. You can be looking into the configurations, you can look at applications, you can always look at different actions. Now since we do not have admin access, the only information we have is to download the client configuration. We can always look at the history server, which can give us information of all the applications which have successfully completed. Now this is from your Yarn UI. What I can also do is I can be going into Hue, which is the web interface, and your web interface also basically allows you to look into the jobs. So you can click on Hue Web UI, and if you have access to that, it should show up, or you should have a way to get to your Hue, which is a graphical user interface, mainly comes with your Cloudera. You can also configure that with Apache. Hortonworks has a different way of giving you the web UI access. You can click and get into Hue, and that is also one way where you can look at Yarn, you can look at the jobs which are running, if there are some issues with it, and these are your web interfaces. So either you look from Yarn web UI, or here in Hue you have something called as job browser, which can also give you information of your different applications which might have run. So here I can just remove this one, which should basically give me a list of all the different kind of jobs or workloads which were run. So either it was a Spark based application, or it was a MapReduce, or it was coming from Hive. So here I have list of all the applications, and it says this was a MapReduce, this was a Spark, something was killed, something was successful, and this was basically probably a Hive query which triggered a MapReduce job. You can click on the application, and that tells you how many tasks were run for it. So there was a map task which ran for it. You can get into the metadata information, which you can also look from the Yarn UI to look into your applications, which can give you a detailed information of if it was a MapReduce, how many map and reduce tasks were run, what were the different counters. If it was a Spark application, it can let you follow through Spark history server or job history server. So you can always use the web UI to look into the jobs. You can be finding in a lot of useful information here. You can also be looking at how many resources were used and what happened to the job. Was it successful? Did it fail? And what was the job status? Now, apart from web UI, which always you might not have access to. So in a particular cluster, in a production cluster, there might be restrictions, and the organization might not have access given to all the users to graphical user interface like Hue, or might be you would not have access to the Cloudera manager or admin console, because probably organization is managing multiple clusters using this admin console. So the one way which you would have access is your web console, or basically your edge node or client machine from where you can connect to the cluster, and then you can be working. So let's log in here, and now here we can give different commands. So this is the command line from where you can have access to different details. You can always check by just typing in MapRed, which gives you different options where you can look at the MapReduce related jobs. You can look at different queues. If there are queues configured, you can look at the history server, or you can also be doing some admin stuff provided you have access. So for example, if I just say MapRed and queue here, this basically gives me an option. Says what would you want to do? Would you want to list all the queues? Do you want information on a particular queue? So let's try a list, and that should give you different queues which were being used. Now here we know that per user a queue dynamically gets created, which is under root.users, and that gives me what is the status of the queue, what is the capacity, has there been any kind of maximum capacity or capping done. So we get to see a huge list of queues which dynamically get configured in this environment, and then you also look at your root.default. I could have also picked up one particular queue and I could have said show me the jobs. So I could do that. Now here we can also give a yarn command. So let me just clear the screen and I will say yarn, and that shows me different options. So apart from your web interface, something like web UI, apart from your yarn's web UI, you could also be looking for information using yarn commands here. So these are some list of commands which we can check. Now you can just type in yarn and version if you would want to see the version, which basically gives you information of what is the Hadoop version being used and what is the vendor specific distribution version. So here we see we are working on Cloudera's distribution 5.14, which is internally using Hadoop 2.6. Now similarly, you can be doing a yarn application list. So if you give this, that could be an exhaustive list of all the applications which are running or applications which have completed. So here we don't see any applications because right now probably there are no applications which are running. It also shows you could be pulling out different status such as submitted, accepted, or running. Now you could also say I would want to see the services that have finished running. So I could say yarn application list and app states as finished. So here we could be using our command. So I could say yarn application list, and then I would want to see the app states, which gives me the applications which have finished. And we would want to list all the applications which finished. Now that might be applications which succeeded, right? And there is a huge list of application which is coming in from the history server, which is basically showing you the huge list of applications which have completed. So this is one way. And then you could also be searching for one particular application. If you would want to search a particular application, if you have the application ID, you could always be doing a grep. That's a simple way. I could say basically let's pick up this one, and if I would want to search for this, if I would want more details on this, I could obviously do that by calling in my previous command, and you could do a grep if that's what you want to do. And if you would want to search, is there an application which is in the list of my applications that shows my application? I could pull out more information about my application. So I could look at the log files for a particular application by giving the application ID. So I could say yarn logs. Now that's an option. And anytime you have a doubt, just hit enter. It will always give you options what you need to give with a particular command. So I can say yarn logs application ID. Now we copied an application ID and we could just give it here. We could give other options like app owner, or if you would want to get into the container details, or if you would want to check on a particular node. Now here I'm giving yarn logs and then I'm pointing it to an application ID, and it says the log aggregation has not completed. Might be this was an application which was triggered based on a particular interactive shell or based on a particular query. So there is no log existing for this particular application. You can always look at the status of an application. You can kill an application. So here you can be saying yarn application, and then what would you want to do with an application? Hit and enter. It shows you the different options. So we just tried app states. You could always look at the last one which says status. And then for my status, I could be giving my application ID. So that tells me what is the status of this application. It connects to the resource manager. It tells me what's the application ID, what kind of application it was, who ran it, which was the queue, where the job was running, what was the start and end time, what is the progress, the status of it, if it is finished or if it has succeeded. And then it basically gives me also an information of where the application master was running. It gives me the information where you can find this job details in history server if you are interested in looking into. It also gives you a aggregate resource allocation which tells how much GB memory and how many core seconds it used. So this is basically looking out at the application details. Now I could kill an application if the application was already running. I could always do a yarn application minus kill, and then I could be giving my application. Now I could try killing this. However, it would say the application is already finished. If I had an application running and if my application was already given an application ID by resource manager, I could just kill it. I can also say yarn node list, which should give me a list of the node managers. Now this is what we were looking from the yarn web UI, and we were pulling out the information, so we can get this and kind of information from your command line. Always remember and always try to be well accustomed with the command line, so you can do various things from the command line, and then obviously you have the web UIs which can help you with a graphical interface, easily able to access things. Now you could be also starting the resource manager, which we would not be doing here because we are already running in a cluster. So you could give a yarn resource manager. You could get the logs of resource manager if you would want by giving yarn daemon. So we can try that. So you can say yarn and then daemon. So it says it does not find the daemon. So you can give something like this, get level, and here I will have to give the node and the IP address where you want to check the logs of resource manager. So you could be giving this, for which we will have to then get into Cloudera manager to look into the nodes and the IP address. You could be giving a command something like this, which basically gives you the level of the log which you have, and I got this resource manager address from the web UI. Now I can be giving in this command to look into the daemon log, and it basically says you would want to look at the resource manager related log, and you have the log4j which is being used for logging. The kind of level which has been set as info, which can again be changed in the way you're logging the information. Now you can try any other commands also from yarn. For example, looking at the yarn rm admin. So you can always do a yarn rm admin, and this basically gives you a lot of other informations like refreshing the queues or refreshing the nodes, or basically looking at the admin ACLs or getting groups. So you could always get group names for a particular user. Now we could search for a particular user such as yarn or HDFS itself. So I could just say here I would want get groups, and then I could be searching for, say, username HDFS. So that tells me HDFS belongs to a Hadoop group. Similarly, you could search for, say, MapRed, or you could search for yarn. So these are service related users which automatically get created, and you can pull out information related to these. You can always do a refresh nodes kind of command, and that is mainly done internally. This can be useful when you're doing commissioning, decommissioning. But then in case of Cloudera or Hortonworks kind of cluster, you would not be manually giving this command, because if you are doing a commissioning, decommissioning from an admin console, and if you are an administrator, then you could just restart the services which are affected, and that will take care of this. But if you were working in an Apache cluster, and if you were doing commissioning, decommissioning, then you would be using in two commands: refresh nodes, and basically that's for refreshing the nodes which should not be used for processing. And similarly, you could have a command refresh nodes which comes with HDFS. So these are different options which you can use with your yarn on the command line. You could also be using curl commands to get more information about your cluster by giving curl -x and then basically pointing out to your resource manager web UI address. Now here I would like to print out the cluster related metrics, and I could just simply do this, which basically gives me a high level information of how many applications were submitted, how many are pending, what is the reserved resources, what is the available amount of memory or CPU cores, and all the information. Similarly, you can be using the same curl commands to get more information like scheduler information. So you would just replace the metrics with scheduler, and you could get the information of the different queues. Now that's a huge list. We can cancel this, and that would give me the list of all the queues which are allocated and what are the resources allocated for each queue. You could also get cluster information on application IDs and status running of applications running in yarn. So you would have to replace the last bit of it, and you would say I would want to look at the applications, and that gives me a huge list of applications. Then you can do a grep and you can be filtering out specific application related information. Similarly, you can be looking at the nodes. So you can always be looking at node specific information, which gives you how many nodes you have. But this could be mainly used when you have an application which wants to, or a web application which wants to use a curl command and would want to get information about your cluster from an HTTP interface. Now, when it comes to application, we can basically try running a simple or a sample MapReduce job, which could then be triggered on yarn and it would use the resources. Now I can look at my application here and I can be looking into my specific directory, which is this one, which should have a lot of files and directories which we have here. Now I could pick up one of these and I could be using a simple example to do some processing. Let's take up this file. So there is a file and I could run a simple word count, or I could be running a Hive query which triggers a MapReduce job. I could even run a Spark application which would then show that the application is running on the cluster. So for example, if I would say Spark to shell. Now I know that this is an interactive way of working with Spark, but this internally triggers a Spark submit and this runs an application. So here when you do a Spark to shell, by default it will contact yarn, so it gets an application ID. It is running on yarn with the master being yarn, and now I have access to the interactive way of working with Spark. Now if I go and look into applications, I should be able to see my application which has been started here and it shows up here. So this is my application 3827 which has been started on yarn, and as of now we can also look into the yarn UI, and that shows me the application which has been started, which basically has one running container which has one CPU core allocated, 2 GB RAM, and it's in progress, although we are not doing anything there. So we can always look at our applications from the yarn UI, or as I mentioned, from your applications tab within yarn services, which gives us the information, and you can even click on this application to follow and see more information, but you should be given access to that. Now this is just a simple application which I triggered using Spark shell. Similarly, I can basically be running a MapReduce. Now to run a MapReduce, I can say Hadoop jar, and that basically needs a class. So we can look for the default path, which is opt cloudera parcels cdh lib hadoop MapReduce Hadoop MapReduce examples, and then we can look at this particular jar file, and if I hit on enter, it shows me the different classes which are part of this jar. And here I would like to use word count, so I could just give this, I could say word count. Now remember, I could run the job in a particular queue by giving in an argument here. So I could say -d mapred dot job dot queue dot name, and then I can point my job to a particular queue. I can even give different arguments in saying I would want my MapReduce output to be compressed, or I want it to be stored in a particular directory, and so on. So here I have the word count, and then basically what I can be doing is I can be pointing it to a particular input path, and then I can have my output which can be getting stored here. Again, a directory which we need to choose, and I will say output new, and I can submit my job. Now once I've submitted my job, it connects to resource manager. It basically gets a job ID, it gets an application ID, it shows you from where you can track your application. You can always go to the yarn UI and you can be looking at your application and the resources it is using. So my application was not a big one and it has already completed. It triggered one map task, it launched one reduce task. It was working on around 12,466 records, where you have then the output of map, which is these many number of output records, which was then taken by a combiner and finally by a reducer, which basically gives you the output. So this is my yarn application which has completed. Now I could be looking into the yarn UI, and if my job has completed, you might not see your application here. So as of now it shows up here, the word count which I ran. It also shows me my previous Spark shell job. It shows me my application is completed. And if you would want further information on this, you can click and go to the history server if you have been given access to it, or directly go to the history server web UI where your application shows up. It shows how many map and reduce tasks it was running. You can click on this particular application, which basically gives you information of your map and reduce tasks. You can look at different counters for your application, right? You can always look at map specific tasks. You can always look into one particular task, what it did, on which node it was running, or you can be looking at the complete application log. So you can always click on the logs, and here you have click here for full log, which gives you the information, and you can always look for your application, which can give you information of app master being launched. Or you could have search for the word container, so you could see a job which needs one or multiple containers, and then you could say container is being requested. Then you could see container is being allocated. Then you can see what is the container size, and then basically your task moves from initializing to running in the container. And finally, you can even search for release, which will tell you that the container was released. So you can always look into the log for more information. So this is how you can interact with Yarn. This is how you can interact with your command line to look for more information, or using your Yarn web UI.
My name is Richard Kirshner. I am with the Simplilearn team. That's www.simplilearn.com. Get certified, get ahead. Today we're going to dive in on Sqoop, one of the many features of the Hadoop ecosystem for the Hadoop file system. What's in it for you? Today we're going to cover the need for Sqoop, what is Sqoop, Sqoop features, Sqoop architecture, Sqoop import, Sqoop export, Sqoop processing, and then finally we'll have a little hands-on demo on Sqoop so you can see what it looks like. So where does the need for Sqoop come in our big data Hadoop file system? Processing huge volumes of data requires loading data from diverse sources into Hadoop cluster. And you can see here we have our data processing, and this process of loading data from the heterogeneous sources comes with a set of challenges. So what are the challenges? Maintaining data consistency, ensuring efficient utilization of resources, especially when you're talking about big data. We can certainly use up the resources when importing terabytes and petabytes of data over the course of time. Loading bulk data to Hadoop was not possible. This is one of the big challenges that came up when they first had the Hadoop file system going. And loading data using script was very slow. In other words, you'd write a script in whatever language you were in, and then it would very slowly load each piece and parse it in. So the solution? Sqoop. Sqoop helped in overcoming all the challenges to traditional approach and could lead bulk data from RDBMS to Hadoop very easily. So think your enterprise server, you want to take the from MySQL or your SQL, and you want to bring that data into your Hadoop warehouse, your data filing system. And that's where Sqoop comes in. So what exactly is Sqoop? Sqoop is a tool used to transfer bulk of data between Hadoop and external data stores, such as relational databases, and MySQL Server, or the Microsoft SQL Server, or MySQL Server. So Sqoop equals SQL plus Hadoop. And you can see here where we have our RDBMS, all the data we have stored on there, and then your Sqoop is the middle ground, and it brings the import into the Hadoop file system. It also is one of the features that goes out and grabs the data from Hadoop and exports it back out into an RDBMS. Let's take a look at Sqoop features. Sqoop features has parallel import and export. It has import results of SQL query, connectors for all major RDBMS databases, Kerberos security integration, provides full and incremental load. So when we look at parallel import and export, Sqoop uses Yarn, yet another resource negotiator, framework to import and export data. This provides fault tolerance on top of parallelism. Sqoop allows us to import the result returned from an SQL query into the Hadoop file system, or the HDFS. And you can see here where the import results of SQL query come in. Sqoop provides connectors for multiple relational database management system, RDBMSs, databases, such as MySQL and Microsoft SQL Server. And it has connectors for all major RDBMS databases. Sqoop supports Kerberos, Computer Network Authentication Protocol, that allows nodes communicating over a non-secure network to prove their identity to one another in a secure manner. Sqoop can load the whole table or parts of the table by a single command. Hence, it supports full and incremental load. Let's dig a little deeper into the Sqoop architecture. We have our client, in this case a hooded wizard behind his laptop. You never know who's going to be accessing the Hadoop cluster. And the client comes in and sends their command, which goes into Sqoop. The client submits the import-export command to import or export data. Data from different databases is fetched by Sqoop. And so you have your enterprise data warehouse, document-based systems. You have a connector for your data warehouse, a connector for document-based systems, which reaches out to those two entities. And we have our connector for the RDBMS. So connectors help in working with a range of popular databases. Multiple mappers perform map tasks to load the data onto HDFS, the Hadoop file system. And you can see here we have the map task. If you remember from Hadoop, Hadoop is based on MapReduce. Because we're not reducing the data, we're just mapping it over, it only accesses the mappers, and it opens up multiple mappers to do parallel processing. And you can see here the HDFS HBase Hive is where the target is for this particular one. Similarly, multiple map tasks will export the data from HDFS onto RDBMS using Sqoop export command. So just like you can import it, you can now export it using the multiple map routines. Sqoop import. So here we have our RDBMS data store, and we have the folders on there. So maybe it's your company's database, maybe it's an archive at Google with all the searches going on, whatever it is. Usually you think with Sqoop, you think SQL, you think MySQL Server or Microsoft SQL Server, that kind of setup. So it gathers the metadata, and you see the Sqoop import. So introspect database to gather metadata, primary key information. And then it submits. So you can see it submits map only job. Remember we talked about MapReduce? It only needs the map side of it because we're not reducing the data, we're just mapping it over. Sqoop divides the input data set into splits and uses individual map tasks to push the splits into HDFS. So right into the Hadoop file system. And you can see down on the right is kind of a small depiction of a Hadoop cluster. And then you have Sqoop export. So we're going to go the other direction. And with the other direction, you have your Hadoop file system storage, which is your Hadoop cluster. You have your Sqoop job, and each one of those clusters then gets a map. The mapper comes out to each one of the computers that has data on it. So the first step is you've got to gather the metadata. So step one, you gather the metadata. Step 2, submits map only job. Introspect database to gather metadata, primary key information. Sqoop divides the input dataset into splits and uses individual map tasks to push the splits to RDBMS. Sqoop will export Hadoop files back to RDBMS tables. And you can think of this in a number of different manners. One of them would be if you're restoring a backup from the Hadoop file system into your enterprise machines. There's certainly many others as far as exploring data and data science. So as we dig a little deeper into Sqoop input, we have our connect, our JDBC, and our URL. So specify the JDBC connect string. Connecting manager, we specify the connection manager class to use. You can see here driver with the class name, manually specify the JDBC driver class to use. Hadoop MapReduce home directory, override Hadoop mapped home, username, set authentication username, and of course help, print usage instructions. And with the export, you'll see that we can specify the JDBC connect string, specify the connection manager class to use, manually specify JDBC driver class to use. You do have to let it know to override the Hadoop MapReduce home, and that's true on both of these. And set authentication username, and finally you can print out all your help setup. So you can see the format for Sqoop is pretty straightforward, both import and export. So let's continue on our path and look at Sqoop processing and what the computer goes through for that. And when we talk about Sqoop processing, first Sqoop runs in the Hadoop cluster. It imports data from the RDBMS, the NoSQL database, to the Hadoop file system. So remember, it might not be importing the data from a RDBMS. It might actually be coming from a NoSQL, and there's many out there. It uses mappers to slice the incoming data into multiple formats and load the data into HDFS. It exports data back into an RDBMS while making sure that the schema of the data in the database is maintained. So now that we've looked at the basic commands in our Sqoop and the Sqoop processing, or at least the basics as far as theory is concerned, let's just jump in and take a look at a demo on Sqoop. For this demo, I'm going to use our Cloudera Quick Start. If you've been watching our other demos we've done, you'll see that we've been using that pretty consistently. Certainly this will work in any of your Horton Sandbox, which is also a single node testing machine. Cloudera is one of them. There's a Docker version instead of VirtualBox. And you can also set up your own Hadoop cluster. Plan a little extra time. If you're not an admin, it's actually a pretty significant endeavor. For an admin, if you've been adminning Linux machines for a very long time and you know a lot of the commands, I find it for most admins it takes them about 2 to 4 hours the first time they go in and create a virtual machine and set up their own Hadoop. In this case though, when you're just learning and getting set up, best to start with Cloudera. Cloudera also includes an install version of MySQL. That way you don't have to worry about installing the SQL version for importing data from and to. Once you're in the Cloudera Quick Start, you'll see it opens a nice CentOS Linux interface, and it has the desktop set up on there. This is really nice for learning, so you're not just looking at command lines. And from in here, it should open up by default to Hue. If not, you can click on Hue. Hue's a kind of a fun little web-based interface. Under Hue, I can go under Query, I can pick an editor, and we'll go right down to Sqoop. So now I'm just going to load the Sqoop editor in our Hue. Now I'm going to switch over and do this all in command line. I just want to show that you can actually do this in Hue through the web-based interface. The reason I like to do the command line is specifically on my computer, it runs much quicker. Or if I do the command line here and I run it, it tends to have an extra lag or an added layer in it. So for this, we're going to go ahead and open our command line. The second reason I do this is we're going to need to go ahead and edit our MySQL so we have something to scoop in. Otherwise, I don't have anything going in there. And of course, we'll zoom in this and increase the size of our screen. So for this demo, our hands-on, I'm going to use Oracle VirtualBox Manager and the Cloudera Quick Start. If you're not familiar with this, we do have another tutorial we put out, and you can send a note in the YouTube video below and let our team know, and they'll send you a link. Or come visit www.Simplilearn.com. Now this creates a Linux box on my Windows computer, so we're going to be in Linux, and it'll be the Cloudera version with Sqoop. It will also be using MySQL. MySQL Server. Once inside the Cloudera VirtualBox, we'll go under the Hue editor. Now we're going to do everything in terminal window, but I just want you to be aware that under the Hue editor, you can go under Query, Editor, and you'll see as we come down here, here's our Sqoop on this. So you can run your Sqoop from in here. Now before we do this, we have to do a little exploration in MySQL, a MySQL Server. That way we know what data is coming in. So let me go ahead and open up a terminal window. In Cloudera, you have a terminal window at the top here that you can just click on and open it up. And let me just go ahead and zoom in on here. We'll go View and Zoom in. Now to get into MySQL Server, you simply type in MySQL, and this part will depend on your setup. Now the Cloudera Quick Start comes up that the username is root and the password is Cloudera. Kind of a strange quirk is that you can put a space between the -u and the root, but not between the -p and the Cloudera. Usually you'd put in a -P and then it prompts you for your password on here. For this demo, I don't worry too much about you knowing the password on that, so we'll just go right into MySQL Server since this is the standard password for this quick start. And you can see we're now into MySQL. And we're going to do just a couple of quick commands in here. There's show databases, and you follow by the semicolon. That's standard in most of these shell commands, so it knows it's the end of your shell command. And you'll see in here in the Quick Start, Cloudera Quick Start, the MySQL comes with a standard set of databases. These are just, some of these have to do like with the Oozie, which is the Oozie part of Hadoop, where others of these like customers and employees and stuff like that, those are just for demo purposes. They come as a standard setup in there so that people going in for the first time have a database to play with, which is really good for us so we don't have to recreate those databases. And you will see on the list here we have a retail_db. And then we can simply do use retail_db. This will set that as a default in MySQL. And then we want to go ahead and show the tables. And if we show the tables, you can see under the database, the retail DB database, we have categories, customers, departments, order items, orders, products. So there's a number of tables in here. And we're going to go ahead and just use a standard SQL command. And if you did our Hive language, you'll note, remember it's the same for HQL also on this. We're just going to select star everything from departments. So there's our departments table, and we're going to list everything on the departments table. And you'll see we have about 6 lines in here, and it has a department ID and a department name. 2 for fitness, 3 for footwear, so on and so forth. Now at this point, I can just go ahead and exit, but it's kind of nice to have this data up here so we can look at it and flip back and forth between the screens. So I'm going to open up another terminal window, and we'll go ahead and zoom in on this also. And it isn't too important for this particular setup, but it's always kind of fun to know what your setup you're working with. What is your host name? And so we'll go ahead and just type that in. This is a Linux command, and it's hostname -f. And you see we're on Quick Start Cloudera. No surprise there. Now this next command is going to be a little bit longer because we're going to be doing our first Sqoop command. And I want to do 2 of them. We're going to list databases and list tables. It's going to take just a moment to get through this because there's a bunch of stuff going on here. So we have Sqoop, we have list databases, we have connect. And under the connect command, we need to let it know how we're connecting. We're going to use the JDBC. This is a very standard one, JDBC MySQL. So you'll see that if you're doing an SQL database, that's how you start it off with. And then the next part, this is where you have to go look it up. It's however it was created. So if your admin created a MySQL server with a certain setup, that's what you have to go by. And you'll see that usually they list this as localhost. So you'll see something like localhost sometimes. There's a lot of different formats, but the most common is either localhost or the actual connection. So in this case, we want to go ahead and do Quick Start 3306. And so Quick Start is the name of the localhost database and how it's hosted on here. And when you set up the Quick Start for Hadoop under Cloudera, it's port 3306 is where that's coming in. So that's where all that's coming from. And so there's our path for that. And then we have to put in our password. We type password, and if you look it up, password on the Cloudera Quick Start is Cloudera. And we have to also let it know the username. And again, if you're doing this, you'd probably put in a minus capital. You can actually just do it for a prompt for the password. So if you leave that out, it'll prompt you. But for this, doesn't really matter. I don't care if you see my password. It's the default one for Cloudera Quick Start. And then the username on here is simply root. And then we're going to put our semicolon at the end. And so we have here our full setup, and we go ahead and list the databases. And you'll see, you might get some warnings on here. I haven't run the updates on the Quick Start. I suggest you're not running the updates either if you're doing this for the first time, because it'll do some reformatting on there. And it quickly pops up, and you can see here's all of our the tables we went in there. And if we go back to on the previous window, we should see that these tables match. So here we come in, and here we have our databases, and you can see back up here where we had the CM, customers, employees, and so on. So the databases match. And then we want to go ahead and list the tables for a specific database. So let's go ahead and do that. I'm a very lazy typist, so I'll put the up arrow in. And you can see here, Sqoop list databases. We're just going to go back and change this from databases to list tables. So we want to list the tables in here. Same connection. So most of the connection is the same, except we need to know which tables we're listing. An interesting fact is you can create a table without being under a database. So if you left this blank, it will show the open tables that aren't connected directly to a database or under a database. But what we want to do is right past this last slash on the 3306, we want to put that retail _ DB, because that's the database we're going to be working with. And this will go in there and show the tables listed under that database. And here we go. We got categories, customers, departments, order items, and products. If we flip back here real quick, there it is, the same thing we had. We had categories, customers, departments, order items, and so on. And so let's go ahead and run our first import command. And again, I'm that lazy typer, so we're going to do Sqoop, and instead of list tables, we want to go ahead and import. So there's our import command. And so once we have our import command in there, then we need to tell it exactly what we're going to import. So everything else is the same. We're importing from the retail DB, so we keep that. And then at the very end, we're going to tag on -- table. That tells it, so we can tell it what table we're importing from. And we're going to import departments. There we go. So this is pretty straightforward, because what's nice about this is you can see the commands are the same. I got the same connection. I change it for whatever database I'm in. Then I come in here, our password and the username are going to be the same. That's all under the MySQL Server setup. And then we let it know what table we're entering in. We run this, and this is going to actually go through the mapper process in Hadoop. So this is a mapping process. It takes the data and it maps it up to different parts in the setup in Hadoop on there, and then saves that data into the Hadoop file system. And it does take it a moment to zip through, which I kind of skipped over for you, since it is running it's designed to run across a cluster, not on a single node. So when you're running on a single node, it's going to run slow, even if you dedicate a couple cores to it. I think I put dedicated 4 cores to this one. And so you can see right down here, we get to the end. It's now mapped in that information. And then we can go in here, we can go under, can flip back to our Hue. And under Hue, on the top, there's databases, and the second icon over is your Hadoop file system. And we can go in here and look at the Hadoop file system, and you'll see it show up underneath our documents. There it is, departments, Cloudera departments. And you can see there's always a delay when I'm working in Hue, which I don't like. And that's the quick start issue. That's not necessarily running it on a server. When I'm running it on a server, you pretty much have to run through some kind of server interface. I still prefer the terminal window. It still runs a lot quicker. But we'll flip back on over here to the command line, and we can do the Hadoop, type in the Hadoop FS, and then list -ls. And if we run this, you'll see underneath our Hadoop file system, there is our departments, which has been added in. And we can also do Hadoop FS, and this is kind of interesting. For those who've gone through the Hadoop file system, everything, you'll recognize this on here. But I'm going to list the contents of departments, and you'll see underneath departments we have part M 000, 001, 002, 003. And so this is interesting because this is how Hadoop saves these files, and this is in the file system. This is not in Hive. So we didn't directly import this into Hive. We put this in the Hadoop file system. Depending on what you're doing, you would then write the schema for Hive to look at the Hadoop file system. Certainly visit our Hive tutorial for more information on Hive specific. So you can see in here are different files that it forms that are part of departments. And we can do something like this. We can look at the contents of one of these files, fs -ls, or a number of the files. And we'll simply do the full path, which is user Cloudera. And then we already know the next one is departments. And then after departments, we're going to put /part star. So this is going to say anything that has part in it. So we have part-m, 000, and so on. We can go ahead and use that cat command or that list command to bring those up. And then we can use the cat command to actually display the contents. And that's a Linux command, Hadoop Linux command, to catenate. Not to be confused with catatonic, catastrophic. There's a lot of cat got your tongue. And we see here fitness, footwear, apparel. That should look really familiar because that's what we had in our MySQL server. When we went in here, we did a select all on here. There it is, fitness, footwear, apparel, golf, outdoors, and fan shop. And then, of course, it's really important, let's flip back on over here, to be able to tell it where to put the data. So we go back to our import command. So here's our Sqoop import. We have our connect. We have the DB underneath our connection, our MySQL server. We have our password, our username, the table where it's going to. The table where it's coming from. And then we can add a target on here. We can put in target dash directory, and you do have to put the full path. That's a Hadoop thing. It's a good practice to be in. And we're going to add it to department, we'll just do department 1. And so here we now add a target directory in here and user Cloudera department 1. And this will take just a moment before, so I'll go ahead and skip over the process since it's going to run very slowly. It's only running on, like I said, a couple cores, and it's also on a single node. And now we can do the Hadoop. Let's just do the up arrow. File system list. We want just straight list. And when we do the Hadoop file system -ls or list, you'll see that we now have department 1. And we can, of course, do list department 1. And you can see we have the files inside department 1, and they mirrored what we saw before with the same files in there, in the part MMO 00 and so on. If we want to look at them, it'd be the same thing we did before with the cat, except instead of departments, we'd be department 1. There we go. And then that's going to come up with the same data we had before. Now, one of the important things when you're importing data, and it's always a question to ask, is do you filter the data before it comes in? Do we want to filter this data as it comes in so we're not storing everything in our file system? You would think Hadoop, big data, put it all in there. I know from experience that putting it all in there can turn a couple hundred terabytes into a petabyte very rapidly. And suddenly you're having to really add on to that data store, and you're storing duplicate data sometimes. So you really need to be able to filter your data out. And so let's go ahead and use our up arrow to go to our last import, since it's still a lot the same stuff. So we have all of our commands under import. We have the target. We're going to change this to department 2. So we're going to create a new directory for this one. And then after departments, there's another command that we didn't really slide in here, and that's our mapping. And I'll show you what this looks like in a minute. But we're going to put M3 in there. That does have nothing to do with the filtering. I'll show you that in a second, though, what that's for. And we just want to put in where. So where, and what is the where? In this case, we want to know where department ID, and if you want to know where that came from, we can flip back on over here. We have department underscore IDs. This is where that's coming from. That's just the name of the column on here. And so we come in here to department ID is greater than 4. Simple logic there. You can see where you'd use that for maybe creating buckets for ages, age from 10 to 15, 20 to 30. You might be looking for, there's all kinds of reasons why you could use the where command on here and filter information out. Maybe you're doing word counting and you want to know words that are used less than 100 times. You want to get rid of the and is and all the stuff that's used over and over again. So we'll go ahead and put the where, and then department ID is greater than 4. We'll go ahead and hit enter on here, and this will create our department 2 setup on this. And I'll go ahead and skip over some of the runtime. Again, it runs really slow on a single node. Real quick page through our commands. Let's see, here we go. Our list, and we should see underneath the list the department 2 on here now, and there it is, department 2, and then I can go ahead and do list department 2. You'll see the contents in here, and you'll see that there is only 3 maps, and it could be that the data created 3 maps, but remember I set it up to only do 3 mappers. So there's 0, 1, and 2, and we can go ahead and do a cat on there. Remember, this is department 2, so we want to look at all the contents of these 3 different files, and there it is. It's greater than 4. So we have golf is 5, outdoor 6, fan shop is 7. So we've effectively filtered out our data and just storing the data we want on our file system. So if you're going to store data on here, the next stage is to export the data. Remember, a lot of times you have MySQL Server and we're continually dumping that data into our long-term storage and access, the Hadoop file system. But what happens when you need to pull that data out and restore a database? Or maybe you have, you just merged with a new company, a favorite topic, merging companies and merging databases. That's listed under Nightmare, and how many different names for company can you have? So you can see where being able to export is also equally important, and let's go ahead and do that. And I'm going to flip back over to MySQL Server here, and we'll need to go ahead and create our database we're going to export into. Now, I'm not going to go too much in detail on this command. We're simply creating a table, and the table is going to have, it's pretty much the same table we already have in here from departments. But in this case, we're going to create a table called DEPT. So it's the same setup, but it's just we're just giving it a different name, a different schema. And so we've done that, and we'll go ahead and do a select star from DEPT. There we go, and it's empty. That's what we expect, a new database, a new data table, and it's empty in there. So now we need to go ahead and export our data that we just filtered out into there. So let's flip back on over here to our Sqoop setup, which is just our Linux terminal window. And let's go back up to one of our commands. Here's Sqoop import. In this case, instead of import, we're going to take the Sqoop and we're going to export. So we're going to just change that, export. And the connection is going to remain the same. So same connect, same database. We're still doing the retail DB. We have the same password, so none of that changes. The big change here is going to be the table. Instead of departments, remember we changed it and gave it a new name. And so we want to change it here also, DEPT. So department. We're not going to worry about the mapper count. And the where was part of our import. There we go. And then finally, it needs to know where to export from. So instead of target directory, we have an export directory. That's where it's coming from. Still user, Cloudera, and we'll keep it as department 2, just so you can see how that data is coming back with that we filtered in. And let's go ahead and run this. It'll take it just a moment to go through its steps. And again, because it's slow, I'm just going to go ahead and skip this so you don't have to sit through it. And once we've wrapped up our export, we'll flip back on over here to MySQL. Use the up arrow And this time we're going to select star from department, and we can see that there it is. It exported the golf outdoors and fan shop. And you can imagine also that you might have to use the where command in your export also. So there's a lot of mixing. The command line for Sqoop is pretty straightforward. You're changing the different variables in there, whether you're creating a table, listing databases. Very powerful tool for bringing your data into the Hadoop file system and exporting it. So now that we've wrapped up our demo on Sqoop and gone through a lot of basic commands, that wraps it up for us today. First, we're going to start with the history of Hive. What is Hive? Architecture of Hive, data flow in Hive, Hive data modeling, Hive data types, different modes of Hive, and difference between Hive and RDBMS. Finally, we're going to look into the features of Hive and do a quick hands-on demo on Hive in the Cloudera Hadoop file system. Let's dive in with a brief history of Hive. So the history of Hive begins with Facebook. Facebook began using Hadoop as a solution to handle the growing big data. And we're not talking about a data that fits on 1 or 2 or even 5 computers. We're talking data that fits on, if you've looked at any of our other Hadoop tutorials, you'll know we're talking about very big data and data pools. And Facebook certainly has a lot of data it tracks. As we know, the Hadoop uses MapReduce for processing data. MapReduce required users to write long codes. And so you'd have these really extensive Java codes, very complicated for the average person to use. Not all users were versed in Java and other coding languages. This proved to be a disadvantage for them. Users were comfortable with writing queries in SQL. SQL has been around for a long time, the standard SQL query language. Hive was developed with the vision to incorporate the concepts of tables, columns, just like SQL. So why Hive? Well, the problem was for processing and analyzing data, users found it difficult to code as not all of them were well versed with the coding languages. You have your processing, you have your analyzing, and so the solution was required a language similar to SQL, which was well known to all the users. And thus the Hive or HQL language evolved. What is Hive? Hive is a data warehouse system which is used for querying and analyzing large data sets stored in the HDFS or the Hadoop file system. Hive uses a query language that we call HiveQL or HQL, which is similar to SQL. So if we take our user, the user sends out their Hive queries, and then that is converted into a MapReduce tasks and then accesses the Hadoop MapReduce system. Let's take a look at the architecture of Hive. Architecture of Hive. We have the Hive client. So that could be the programmer, or maybe it's a manager who knows enough SQL to do a basic query to look up the data they need. The Hive client supports different types of client applications in different languages for performing queries. And so we have our Thrift application and the Hive Thrift client. Thrift is a software framework. Hive server is based on Thrift, so it can serve the requests from all programming languages that support Thrift. And then we have our JDBC application and the Hive JDBC driver. JDBC, Java Database Connectivity. JDBC application is connected through the JDBC driver. And then you have the ODBC application, or the Hive ODBC driver. The ODBC, or Open Database Connectivity, the ODBC application is connected through the ODBC driver. With the growing development of all of our different scripting languages, Python, C++, Spark, Java, you can find just about any connection in any of the main scripting languages. And so we have our Hive services. As we look deeper into the architecture, Hive supports various services. So you have your Hive server, basically your Thrift application or your Hive Thrift client or your JDBC or your Hive JDBC driver, your ODBC application or your Hive ODBC driver. They all connect into the Hive server. And you have your Hive web interface. You also have your CLI. Now, the Hive web interface is a GUI is provided to execute Hive queries. And we'll actually be using that later on today, so you can see kind of what that looks like and get a feel for what that means. Commands are executed directly in CLI. And then the CLI is a direct terminal window. And I'll also show you that too, so you can see how those two different interfaces work. These then push the code into the Hive driver. Hive driver is responsible for all the queries submitted, so everything goes through that driver. Let's take a closer look at the Hive driver. The Hive driver now performs 3 steps internally. One is a compiler. Hive driver passes query to compiler where it is checked and analyzed. Then the optimizer kicks in, and the optimized logical plan in the form of a graph of MapReduce and HDFS tasks is obtained. And then finally, in the executor, in the final step, the tasks are executed. When we look at the architecture, we also have to note the metastore. Metastore is a repository for Hive metadata. It stores metadata for Hive tables. And you can think of this as your schema and where is it located. And it's stored on the Apache DB. Processing and resource management is all handled by the MapReduce v1. You'll see MapReduce v2, the Yarn, and the Tez. These are all different ways of managing these resources depending on what version of Hadoop you're in. Hive uses MapReduce framework to process queries. And then we have our distributed storage, which is the HDFS. And if you looked at our Hadoop tutorials, you'll know that these are on commodity machines and are linearly scalable. That means they're very affordable. A lot of time when you're talking about big data, you're talking about 1/10 of the price of storing it on enterprise computers. And then we look at the data flow in Hive. So in our data flow in Hive, we have our Hive in the Hadoop system. And underneath the user interface, or the UI, we have our driver, our compiler, our execution engine, and our metastore. That all goes into the MapReduce and the Hadoop file system. So when we execute a query, you can see it coming in here. It goes into the driver, step 1. Step 2, we get a plan. What are we going to do? Refers to the query execution. Then we go to the metadata. And it's like, well, what kind of metadata are we actually looking at? Where is this data located? What is the schema on it? Then it comes back with the metadata into the compiler. Then the compiler takes all that information and the send plan and returns it to the driver. The driver then sends the execute plan to the execution engine. Once it's in the execution engine acts as a bridge between Hive and Hadoop to process the query. And that's going into your MapReduce and your Hadoop file system, or your HDFS. And then we come back with the metadata operations. It goes back into the metastore to update or let it know what's going on, which also goes to it's a communication between the execution engine and the metastore. Execution engine communications is bidirectionally with the metastore to perform operations like create, drop tables. Metastore stores information about tables and columns. So again, we're talking about the schema of your database. And once we have that, we have a bidirectional send results communication back into the driver. And then we have the fetch results, which goes back to the client. So let's take a little bit look at the Hive data modeling. Hive data modeling. So you have your Hive data modeling, you have your tables, you have your partitions, and you have buckets. The tables in Hive are created the same way it is done in RDBMS. So when you're looking at your traditional SQL Server or MySQL Server, where you might have enterprise equipment and a lot of people pulling and moving stuff off of there, the tables are going to look very similar. And this makes it very easy to take that information, and let's say you need to keep current information, but you need to store all of your years of transactions back into the Hadoop Hive. So you match those. Those all kind of look the same. The tables are the same. Your databases look very similar, and you can easily import them back. You can easily store them into the Hive system. Partitions. Here, tables are organized into partitions for grouping same type of data based on partition key. This can become very important for speeding up the process of doing queries. So if you're looking at dates, as far as like your employment dates of employees, if that's what you're tracking, you might add a partition there because that might be one of the key things that you're always looking up as far as employees are concerned. And finally, we have buckets. Data present in partitions can be further divided into buckets for efficient querying. Again, there's that efficiency. At this level, a lot of times you're working with the programmer and the admin of your Hadoop file system to maximize the efficiency of that file system. So it's usually a two-person job when we're talking about Hive data modeling. You want to make sure that they work together and you're maximizing your resources. Hive data types. So we're talking about Hive data types. We have our primitive data types and our complex data types. A lot of this will look familiar because it mirrors a lot of stuff in SQL. In our primitive data types, we have the numerical data types, string data type, date time data type, and miscellaneous data type. And these should be they're kind of self-explanatory, but just in case. Numerical data is your floats, your integers, your short integers. All of that numerical data comes in as a number. A string, of course, is characters and numbers. And then you have your date timestamp, and then we have kind of a general way of pulling your own created data types in there. That's our miscellaneous data type. And we have complex data types. So you can store arrays, you can store maps, you can store structures, and even units in there. As we dig into Hive data types, and we have the primitive data types and the complex data types. So we look at primitive data types, and we're looking at numeric data types. Data types like an integer, a float, a decimal, those are all stored as numbers in the Hive data system. A string data types like characters and strings. You store the name of the person you're working with, John Doe, the city, Memphis, the state, Tennessee, maybe it's Boulder, Colorado, USA, or maybe it's Hyderabad, India. That's all going to be string and stored as a string character. And of course we have our date time data type. Data types like timestamp, date, interval. Those are very common as far as tracking cells, anything like that. So you can just think if you can type a stamp of time on it, or maybe you're dealing with a race and you want to know the interval, how long did the person take to complete whatever task it was. All of that is date time data type. And then we talk miscellaneous data type. These are like Boolean and binary. And when you get into Boolean and binary, you can actually almost create anything in there. But your yes, no's, 0, 1. Now let's take a look at complex data types a little closer. We have arrays. So your syntax is of data type, and it's an array. And you can just think of an array as a collection of same entities, 1, 2, 3, 4, if they're all numbers. And you have maps. This is a collection of key value pairs. So understanding maps is so central to Hadoop. So when we store maps, you have a key, which is a set. You can only have one key per mapped value. And so in Hadoop, of course, you collect the same keys and you can add them all up or do something with all the contents of the same key. But this is our map as a primitive type data type in our collection of key value pairs. And then collection of complex data with comment. So we can have a structure where you have like column name, data type, comment, column comment. So you can get very complicated structures in here with your collection of data and your commented setup. And then we have units, and this is a collection of heterogeneous data types. So the syntax for this is union type, data type, and so on. So it's all going to be the same. A little bit different than the arrays where you can actually mix and match. Different modes of Hive. Hive operates in two modes depending on the number and size of data nodes. We have our local mode and our MapReduce mode. When we talk about the local mode, it is used when Hadoop is having one data node and the data is small. Processing will be very fast on a smaller data sets, which are present in local machine. And this might be that you have a local file of stuff you're uploading into the Hive, and you need to do some processes in there. You can go ahead and run those Hive processes and queries on it. Usually, you don't see much in the way of a single node Hadoop system. If you're going to do that, you might as well just use like an SQL database or even a Java SQLite or something. Python is SQLite. So you don't really see a lot of single node Hadoop databases, but you do see the local mode in Hive where you're working with a small amount of data that's going to be integrated into the larger database. And then we have the MapReduce mode. This is used when Hadoop is having multiple data nodes and the data is spread across various data nodes. Processing large data sets can be more efficient using this mode. And this you can think of, instead of it being 1, 2, 3, or even 5 computers, we're usually talking with the Hadoop file system, we're looking at 10 computers, 15, 100, where this data is spread across all those different Hadoop nodes. Difference between Hive and RDBMS. And remember, RDBMS stands for the Relational Database Management System. Let's take a look at the difference between Hive and the RDBMS. With Hive enforces schema on read. And it's very important that whatever's coming in, that's when Hive's looking at it and making sure that it fits the model. The RDBMS enforces a schema when it actually writes the data into the database. So it's read the data, and then once it starts to write it, that's where it's going to give you the error or tell you something's incorrect about your scheme. Hive data size is in petabytes. That is hard to imagine. When we're looking at your personal computer on your desk, maybe you have 10 terabytes if it's a high-end computer. But we're talking petabytes, so that's hundreds of computers grouped together. When an RDBMS, data size is in terabytes. Very rarely do you see an RDBMS system that's spread over more than 5 computers. And there's a lot of reasons for that. With the RDBMS, it actually has a high-end amount of writes to the hard drive. There's a lot more going on there. You're writing and pulling stuff, so you really don't want to get too big with an RDBMS or you're going to run into a lot of problems. With Hive, you can take it as big as you want. Hive is based on the notion of write once and read many times. This is so important. They call it worm, which is write, W, once, O, read, R, many times, M. They refer to it as worm, and that's true of a lot of your Hadoop setup. It's altered a little bit, but in general, we're looking at archiving data that you want to do data analysis on. We're looking at pulling all that stuff off your RDBMS from years and years and years of business or whatever your company does or scientific research and putting that into a huge data pool so that you can now do queries on it and get that information out of it. With the RDBMS, it's based on the notion of read and write many times. So you're continually updating this database. You're continually bringing up new stuff, new cells. The count changes because they have a different licensing now, whatever software you're selling, all that kind of stuff where the data is continually fluctuating. And then Hive resembles a traditional database by supporting SQL, but it is not a database. It is a data warehouse. This is very important, and it goes with all the other stuff we've talked about, that we're not looking at a database but a data warehouse to store the data and still have fast and easy access to it for doing queries. You can think of Twitter and Facebook. They have so many posts that are archived back historically. Those posts aren't going to change. They made the post, they're posted, they're there, and they're in their database, but they have to store it in a warehouse in case they want to pull it back up. With the RDBMS, it's a type of database management system which is based on the relational model of data. And then with Hive, easily scalable at a low cost. Again, we're talking maybe $1,000 per terabyte. The RDBMS is not scalable at a low cost. When you first start on the lower end, you're talking about $10,000 per terabyte of data, including all the backup on the models and all the added necessities to support it. As you scale it up, you have to scale those computers and hardware up. So you might start off with a basic server, and then you upgrade to a Sun computer to run it, and you spend tens of thousands of dollars for that hardware upgrade. With Hive, you just put another computer into your Hadoop file system. So let's look at some of the features of Hive. When we're looking at the features of Hive, we're talking about the use of SQL-like language called HiveQL. A lot of times you'll see that as HQL, which is easier than long codes. This is nice if you're working with your shareholders. You come to them and you say, hey, you can do a basic SQL query on here and pull up the information you need. This way, you don't have to have your programmers jump in every time they want to look up something in the database. They actually now can easily do that if they're not skilled in programming and script writing. Tables are used which are similar to the RDBMS, hence easier to understand. And one of the things I like about this is when I'm bringing tables in from a MySQL server or SQL server, there's almost a direct reflection between the two. So when you're looking at one, which is a data which is continually changing, and then you're going into the archive database, it's not this huge jump where you have to learn a whole new language. You mirror that same schema into the HDFS, into the Hive, making it very easy to go between the two. And then using HiveQL, multiple users can simultaneously query data. So again, you can have multiple clients in there and they send in their query. That's also true with the RDBMS, which kind of queues them up. Because it's running so fast, you don't notice the lag time. Well, you get that also with the HQL. As you add more computers in, the query can go very quickly, depending on how many computers and how much resources each machine has to pull the information. And Hive supports a variety of data types. So with Hive, it's designed to be on the Hadoop system, which you can put almost anything into the Hadoop file system. So with all that, let's take a look at a demo on HiveQL or HQL. Before I dive into the hands-on demo, let's take a look at the website, hive.apache.org. That's the main website since Apache. It's an Apache open source software. This is the main software or the main site for the build. And if you go in here, you'll see that they're slowly migrating Hive into Beehive. And so if you see Beehive versus Hive, note the Beehive is the new release is coming out. That's all it is. It reflects a lot of the same functionality of Hive. It's the same thing. And then we like to pull up some kind of documentation on commands. And for this, I'm actually going to go to Hortonworks Hive cheat sheet. And that's because Hortonworks and Cloudera are two of the most common used builds for Hadoop and for which include Hive and all the different tools in there. And so Hortonworks has a pretty good PDF you can download cheat sheet on there. I believe Cloudera does too, but we'll go ahead and just look at the Horton one, because it's the one that comes up really good. And you can see when we look at the query language, it compares MySQL Server to Hive QL or HQL. And you can see the basic select. We select from columns, from table where conditions exist. You know, most basic command on there. And they have different things you can do with it, just like you do with your SQL. And if you scroll down, you'll see data types. So here's your integer, your float, your binary, double string, timestamp, and all the different data types you can use. Some different semantics, different keys, features, functions for running a Hive query, command line setup, and of course the Hive shell setup in here. So you can see right here, if we loop through it, it has a lot of your basic stuff. And we're basically looking at SQL across a Horton database. We're going to go ahead and run our Hadoop cluster Hive demo. And I'm going to go ahead and use the Cloudera Quick Start. And this is in the virtual box. So again, we have an Oracle virtual box, which is open source. And then we have our Cloudera Quick Start, which is the Hadoop setup on a single node. Now, obviously, Hadoop and Hive are designed to run across a cluster of computers. So when we talk about a single node, is for education, testing, that kind of thing. And if you have a chance, you can always go back and look at our demo we had on setting up a Hadoop system in a single cluster. Just set a note down below in the YouTube video, and our team will get in contact with you and send you that link if you don't already have it. Or you can contact us at the www.simplilearn.com. Now in here, it's always important to note that you do need on your computer, if you're running on Windows, because I'm on a Windows machine, you're going to need probably about 12 gigabytes to actually run this. It used to be you could get by with a lot less, but as things have evolved, they take up more and more resources. And you need the professional version. If you have the home version, I was able to get that to run, but boy, did it take a lot of extra work to get the home version to let me use the virtual setup on there. And we'll simply click on the Cloudera Quick Start, and I'm going to go and just start that up. And this is starting up our Linux. So we have our Windows 10, which is the computer I'm on, and then I have the virtual box, which is going to have a Linux operating system in it. And we'll skip ahead so you don't have to watch the whole install. Something interesting to know about the Cloudera is that it's running on Linux CentOS, and for whatever reason, I've always had to click on it and hit the escape button for it to spin up. And then you'll see the DOS come in here. Now that our Cloudera is spun up on our virtual machine with the Linux on, we can see here we have our, it uses the Thunderbird browser on here by default and automatically opens up a number of different tabs for us. And a quick note, because I mentioned like the restrictions on getting set up on your own computer. If you have a home edition computer and you're worried about setting it up on there, you can also go in there and spin up a 1-month free service on Amazon Web Service to play with this. So there's other options. You're not stuck with just doing it on the quick start menu. You can spin this up in many other ways. Now the first thing we want to note is that we've come in here into Cloudera, and I'm going to access this in 2 ways. The first one is we're going to use Hue. And I'm going to open up Hue, and it'll take it a moment to load from the setup on here. And Hue is nice. If I go in and use Hue as an editor into Hive or into the Hadoop setup, usually I'm doing it as a from an admin side because it has a lot more information, a lot of visuals, less to do with actually diving in there and just executing code. And you can also write this code into files and scripts, and there's other ways you can upload it into Hive. But today we're going to look at the command lines, and we'll upload it into Hue, and then we'll go into and actually do our work in a terminal window under the Hive shell. Now in the Hue browser window, if you go under Query and click on the pull down menu, and then you go under Editor, and you'll see Hive. There we go. There's our Hive setup. I go and click on Hive, and this will open up our query down here, and now it has a nice little B that shows our Hive going, and we can go something very simple down here like show databases, and we follow it with the semicolon. And that's the standard in Hive, is you always add our punctuation at the end there. And I'll go ahead and run this, and the query will show up underneath. And you'll see down here, since this is a new quick start I just put on here, you'll see it has the default down here for the databases. That's the database name. I haven't actually created any databases on here. And then there's a lot of other like assistant function, tables, your databases up here. There's all kinds of things you can research, you can look at through Hue as far as a bigger picture. The downside of this is it always seems to lag. For me, whenever I'm doing this, I always seem to run slow. So if you're in Cloudera, you can open up a terminal window. They actually have an icon at the top. You can also go under Applications, and under Applications, System Tools, and Terminal. Either one will work. It's just a regular terminal window. And this terminal window is now running underneath our Linux. So this is a Linux terminal window, or on our virtual machine, which is resting on our regular Windows 10 machine. And we'll go ahead and zoom this in so you can see the text better on your own video. And I simply just clicked on View and Zoom in. And then all we have to do is type in Hive. And this will open up the shell on here. And it takes it just a moment to load. When starting up Hive, I also want to note that depending on your rights on the computer you're on in your action, you might have to do sudo hive and put in your password and username. Most computers are usually set up with the Hive login. Again, it just depends on how you're accessing the Linux system and the Hive shell. Once we're in here, we can go ahead and do a simple HQL command, show databases. And if we do that, we'll see here that we don't have any databases. So we can go ahead and create a database. And we'll just call it Office for today, for this moment. Now if I do show, we'll just do the up arrow. Up arrow is a hotkey that works in both Linux and in Hive. So I can go back and paste through all the commands I've typed in. And we can see now that I have my, there's of course the default database, and then there's the Office database. So now we've created a database. It's pretty quick and easy. And we can go ahead and drop the database. We can do drop database Office. Now this will work on this database because it's empty. If your database was not empty, you would have to do cascade. And that drops all the tables in the database and the database itself. Now if we do show database, and we'll go ahead and recreate our database because we're going to use the Office database for the rest of this hands-on demo. A really handy command to now set with the SQL or HQL is to use Office. And what that does is that sets Office as the default database. So instead of having to reference the database every time we work with a table, it now automatically assumes that's the database being used, whatever tables we're working on. The difference is you put the database name period table. And I'll show you in just a minute what that looks like and how that's different. If we're going to have a table and a database, we should probably load some data into it. So let me go ahead and switch gears here and open up a terminal window. You can just open another terminal window and it'll open up right on top of the one that you have Hive shell running in. And when we're in this terminal window, first we're going to go ahead and just do a list, which is of course a Linux command. You can see all the files I have in here. This is the default load. We can change directory to documents. We can list in documents, and we're actually going to be looking at employee.csv. A Linux command is the cat. You can use this actually to combine documents. There's all kinds of things that cat does. But if we want to just display the contents of our employee.csv file, we can simply do cat employee CSV. And when we're looking at this, we want to know a couple things. One, there's a line at the top. Okay, so the very first thing we notice is that we have a header line. The next thing we notice is that the data is comma separated. And in this particular case, you'll see a space here. Generally, with these, you got to be real careful with spaces. There's all kinds of things you got to watch out for because they can cause issues. These spaces won't, because these are all strings that the space is connected to. If this was a space next to the integer, you would get a null value that comes into the database without doing something extra in there. Now, with most of Hadoop, that's important to know that you're writing the data once, reading it many times. And that's true of almost all your Hadoop things coming in. So you really want to process the data before it gets into the database. And for those of you who have studied data transformation, that's the ETL, where you extract, transfer, form, and then load the data. So you really want to extract and transform before putting it into the Hive. Then you load it into the Hive with the transformed data. And of course, we also want to note the schema. We have an integer, string, string, integer, integer. So we kept it pretty simple in here as far as the way the data is set up. The last thing that you're going to want to look up is the source. Since we're doing local uploads, we want to know what the path is. We have the whole path. In this case, it's home/Cloudera/documents. And these are just text documents we're working with right now. We're not doing anything fancy. So we can do a simple get edit employee.csv, and you'll see it comes up here. It's just a text document, so I can easily remove these added spaces. There we go. And then we go ahead and just save it. And so now it has the new setup in there. We've edited it. The gedit is usually one of the default that loads into Linux. So any text editor will do. Back to the Hive shell. So let's go ahead and create a table employee. And what I want you to note here is I did not put the semicolon on the end here. A semicolon tells it to execute that line. So this is kind of nice if you can actually just paste it in if you have it written on another sheet. And you can see right here where I have create table employee, and it goes into the next line on there so I can do all of my commands at once. Now, just so I don't have any typo errors, I went ahead and just pasted the next 3 lines in. And the next one is our schema. If you remember correctly from the other side, we had the different values in here, which was ID, name, department, year of joining, and salary. And the ID is an integer, name is a string, department string, year of joining integer, salary an integer. And they're in brackets. So we put closed brackets around them. And you could do this all as one line. And then we have row format delimited fields terminated by comma. And this is important because the default is tabs. So if I do it now, it won't find any terminated fields. So you'll get a bunch of null values loaded into your table. And then finally, our table properties, we want to skip the header line count equals 1. Now, this is a lot of work for uploading a single file. It's kind of goofy when you're uploading a single file that you have to put all this in here. But keep in mind, Hive and Hadoop is designed for writing many files into the database. You write them all in there, and then they're saved. It's an archive. It's a data warehouse. And then you're able to do all your queries on them. So a lot of times, we're not looking at just the one file coming up. We're loading hundreds of files. You have your reports coming off of your main database. All those reports are being loaded. You have your log files. You have, all this different data is being dumped into Hadoop, and in this case, Hive on top of Hadoop. And so we need to let it know, hey, how do I handle these files coming in? And then we have the semicolon at the end, which lets us know to go ahead and run this line. And so we'll go ahead and run that. And now if we do a show tables, you can see there's our employee on there. We can also describe. If we do describe employee, you can see that we have our ID integer, name string, department string, year of joining integer, and salary integer. And then finally, let's just do a select star from employee, very basic SQL and HQL command, selecting data. And it's going to come up, and we haven't put anything in it, so as we expect, there's no data in it. So if we flip back to our Linux terminal window, you can see where we did the cat employee.csv, and you can see all the data we expect to come into it. And we also did our pwd, and right here you see the path. You need that full path when you are loading data. You can do a browse, and if I did it right now with just the employee.csv as a name, it will work. But that is a really bad habit. In general, when you're loading data, because it's you don't know what else is going on in the computer, you want to do the full path almost in all your data loads. So let's go ahead and flip back over here to our Hive shell we're working in. And the command for this is load data. So that says, hey, we're loading data. That's a Hive command, HQL. And we want local data, so you got to put down local in path. So now it needs to know where the path is. Now, to make this more legible, I'm just going to go ahead and hit enter, and then we'll just paste the full path in there, which I have stored over on the side, like a good prepared demo. And you'll see here we have home, Cloudera, documents, employee.csv. So it's a whole path for this text document in here. And we go ahead and hit enter in there, and then we have to let it know where the data is going. So now we have a source, and we need a destination. And it's going to go into the table, and we'll just call it employee. We'll just match the table in there. And because I want it to execute, we put the semicolon on the end. It goes ahead and executes all 3 lines. Now if we go back, if you remember we did the select star from employee, just using the up arrow to page through my different commands I've already typed in. You can see right here we have, as we expect, we have Rose, Sam, Mike, and Nick, and we have all their information showing in our 4 rows. And then let's go ahead and do select and count. We'll just look at a couple of these different select options you can do. We're going to count everything from employee. Now this is kind of interesting because the first one just pops up with a basic select because it doesn't need to go through the full MapReduce phase. But when you start doing a count, it does go through the full MapReduce setup in the Hive and Hadoop. And because I'm doing this demo on a single node Cloudera virtual box on top of a Windows 10, all the benefits of running it on a cluster are gone, and instead it's now going through all those added layers, so it takes longer to run. You know, like I said, when you do a single node, as I said earlier, it doesn't do any good as an actual distribution because you're only running it on one computer, and then you've added all these different layers to run it. And we see it comes up with 4, and that's what we expect. We have 4 rows. We expect 4 at the end. And if you remember from our cheat sheet, which we brought up here from Horton's, it's a pretty good one, there's all these different commands we can do. We'll look at one more command where we do the what they call subqueries right down here, because that's really common to do a lot of subqueries. And so we'll do select star or all different columns from employee. Now if we weren't using the Office database, it would look like this, from office.employee. And either one will work on this particular one because we have Office set as a default on there. So from Office employee, and then the command where creates a subset. And in this case, we want to know where the salary is greater than 25,000. There we go. And of course we end with our semicolon. And if we run this query, you can see it pops up, and there's our salaries of people, top earners. We have Rose in IT and Mike in HR. Kudos to them. Of course, they're fictional. We don't actually have a Rose and a Mike in those positions, or maybe we do. So finally, what we want to go ahead and do is we're done with this table. Now remember, you're dealing with a data warehouse, so you usually don't do a lot of dropping of tables and databases. But we're going to go ahead and drop this table here. Before we drop it, one more quick note is we can change it. So what we're going to do is we're going to alter table, Office employee, and we want to go ahead and rename it. There's some other commands you can do in here, but rename is pretty common, and we're going to rename it to, and it's going to stay in Office, and it turns out one of our shareholders really doesn't like the word employee. He wants employees plural. It's a big deal to him. So let's go ahead and change that name for the table. It's that easy because it's just changing the metadata on there. And now if we do show tables, you'll see we now have employees, not employee. And then at this point, maybe we're doing some house cleaning because this is all practice. So we're going to go ahead and drop table, and we'll drop table employees because we changed the name in there. So if we did employee, it just give us an error. And now if we do show tables, you'll see all the tables are gone. Now the next thing we want to go ahead and take a look at, and we're going to walk back through the loading of data just real quick because we're going to load 2 tables in here. And let me just float back to our terminal window so we can see what those tables are that we're loading. And so up here we have a customer file, and we have an order file. We want to go ahead and put the customers and the orders into here. So those are the 2 we're doing. And of course, it's always nice to see what you're working with. So let's do our cat customer.csv. We could always do gedit, but we don't really need to edit these. We just want to take a look at the data in customer. And important in here is, again, we have a header, so we have to skip a line, comma separated. Nothing odd with the data. We have our schema, which is integer, string, integer, string, integer. So you'd want to take that, note that down, or flip back and forth when you're doing it. And then let's go ahead and do cat order.csv, and we can see we have OID, which I'm guessing is the order ID. We have a date. Oh, something new. We've done integers and strings, but we haven't done date. When you're importing new and you never worked with the date, date's always one of the more trickier fields to port in. And that's true of just about any scripting language I've worked with. All of them have their own idea of how date's supposed to be formatted, what the default is. This particular format, where it's year, and it has all 4 digits, dash month, 2 digits, dash day, is the standard import for the Hive. So you'll have to look up and see what the different formats are if you're going to do a different format in there coming in, or you're not able to pre-process the data. But this would be a pre-processing of the data thing coming in. If you remember correctly from our ETL, which is just in case you weren't able to hear me last time, ETL, which stands for extract, transform, then load. So you want to make sure you're transforming this data before it gets into here. And so we're going to go ahead and bring both this data in here. And really we're doing this so we can show you the basic join. There is, if you remember from our setup, merge, join, all kinds of different things you can do. But joining different data sets is so common. So it's really important to know how to do this. We need to go ahead and bring in these two data sets. And you can see where I just created a table customer. Here's our schema, the integer, name, age, address, salary. Here's our delimited by commas, and our table properties where we skip a line. Well, let's go ahead and load the data first, and then we'll do that with our order. And let's go ahead and put that in here, and I've got it split into 3 lines so you can see it easily. We got load data local in path. So we know we're loading data, we know it's local, and we have the path. Here's the complete path for, oops, this is supposed to be order, CSV. Grab the wrong one. Of course, it's going to give me errors because you can't recreate the same table on there. And here we go, create table. Here's our integer, date, customer, the basic setup that we had coming in here for our schema, row format, commas, table properties, skip header line. And then finally, let's load the data into our order table. Load data local in path, home Cloudera documents order.csv into table order. Now if we did everything right, we should be able to do select star from customer. And you can see we have all 7 customers, and then we can do select star from order, and we have 4 orders. So this is just like a quick frame. We have, a lot of times when you have your customer databases in business, you have thousands of customers from years and years, and some of them, they close their business, they change names, all kinds of things happen. So what we want to do is we want to go ahead and find just the information connected to these orders and who's connected to them. And so let's go ahead and do, it's a select, because we're going to display information. So select, and this is kind of interesting. We're going to do c.id, and I'm going to define C as customer, as a customer table in just a minute. Then we're going to do c.name, and again we're going to define the c.age. So this means from the customer we want to know their ID, their name, their age, and then I'd also like to know the order amount. So let's do O for .amount. And then this is where we need to go ahead and define what we're doing. And I'll go ahead and capitalize from customer. So we're going to take the customer table in here, and we're going to name it C. That's where the C comes from. So that's the customer table C, and we want to join order as O. That's where our O comes from. So the O.amount is what we're joining in there. And then we want to do this on, we got to tell it how to connect the 2 tables, C.id equals O.customer underscore ID. So now we know how they're joined. And now remember, we have 7 customers in here. We have 4 orders. And as it processes, we should get a return of 4 different names joined together. And they're joined based on, of course, the orders on there. And once we're done, we now have the order number, the person who made the order, their age, and the amount of the order, which came from the order table. So you have your different information, and you can see how the join works here. Very common use of tables and HQL and SQL. And let's do one more thing with our database, and then I'll show you a couple other Hive commands. And let's go ahead and do a drop, and we're going to drop database office. And if you're looking at this and you remember from earlier, this will give me an error. And let's just see what that looks like. It says failed to execute, exception, 1 or more tables exist. So if you remember from before, you can't just drop a database unless you tell it to cascade. That lets it know, I don't care how many tables are in it, let's get rid of it. And in Hadoop, since it's a warehouse, a data warehouse, you usually don't do a lot of dropping. Maybe at the beginning when you're developing the schemas and you realize you messed up, you might drop some stuff. But down the road, you're really just adding commodity machines to take up so you can store more stuff on it. So you usually don't do a lot of database dropping. And some other fun commands to know is you can do select round 2.3 as round value. You can do a round off in Hive. We can do as floor value, which is going to give us a 2, so it turns it into an integer versus a float. It goes down, basically truncates it, but it goes down. And we can also do ceiling, which is going to round it up. So we're looking for the next integer above. There's a few commands we didn't show in here because we're on a single node. as an admin to help speediate the process, you usually add in partitions for the data and buckets. You can't do that on a single node because when you add a partition, it partitions it across separate nodes. But beyond that, you can see that it's very straightforward. We have SQL coming in, and all your basic queries that are in SQL are very similar to HQL. Let's get started with Pig. Why Pig? What is Pig? MapReduce versus Hive versus Pig. Hopefully you've had a chance to do our Hive tutorial and our MapReduce tutorial. If you haven't, send a note over to Simplilearn and we'll follow up with a link to you. We'll look at Pig architecture, working of Pig, Pig Latin data model, Pig execution modes, a use case Twitter, and features of Pig. And then we'll tag on a short demo so you can see Pig in action. So, why Pig? As we all know, Hadoop uses MapReduce to analyze and process big data. Processing big data consumed more time. So before we had the Hadoop system, they'd have to expend a lot of money on a huge set of computers and enterprise machines. So he introduced the Hadoop MapReduce. And so afterwards, processing big data was faster using MapReduce. Then what is the problem with MapReduce? Prior to 2006, all MapReduce programs were written in Java. Non-programmers found it difficult to write lengthy Java codes. They faced issues in incorporating map, sort, reduce to fundamentals of MapReduce while creating a program. You can see here map phase, shuffle, and sort reduce phase. Eventually, it became a difficult task to maintain and optimize the code, due to which the processing time increased. You can imagine a manager trying to go in there and needing a simple query to find out data, and he has to go talk to the programmers anytime he wants anything. So that was a big problem. Not everybody wants to have an on-call programmer for every manager on their team. Yahoo faced problems to process and analyze large data sets using Java, as the codes were complex and lengthy. There was a necessity to develop an easier way to analyze large data sets without using time-consuming complex Java modes and codes and scripts and all that fun stuff. Apache Pig was developed by Yahoo. It was developed with the vision to analyze and process large data sets without using complex Java codes. Pig was developed especially for non-programmers. Pig used simple steps to analyze data sets, which was time efficient. So what exactly is Pig? Pig is a scripting platform that runs on Hadoop clusters designed to process and analyze large data sets. And so you have your Pig, which uses SQL-like queries. They're definitely not SQL, but some of them resemble SQL queries. And then we use that to analyze our data. Pig operates on various types of data like structured, semi-structured, and unstructured data. Let's take a closer look at MapReduce versus Hive versus Pig. So we start with a compiled language, your MapReduce. And we have Hive, which is your SQL-like query. And then we have Pig, which is a scripting language. It has some similarities to SQL, but it has a lot of its own stuff. Remember, SQL-like query, which is what Hive is based off, looks for structured data. And so when we get into scripting languages like Pig, now we're dealing more with semi-structured and even unstructured data. With a Hadoop MapReduce, we have a need to write long, complex codes. With Hive, no need to write complex codes. You could just put it in a simple SQL query or HQL, HiveQL. And in Pig, no need to write complex codes, as we have Pig Latin. Now remember, in the MapReduce, it can produce structured, semi-structured, and unstructured data. And as I mentioned before, Hive can process only structured data. Think rows and columns. Where Pig can process structured, semi-structured, and unstructured data. You can think of structured data as rows and columns, semi-structured as your HTML, XML documents like you have on your web pages, and unstructured could be anything from groups of documents in written format, Twitter, tweets, any of those things come in as very unstructured data. And with our Hadoop MapReduce, we have a lower level of abstraction. With both Hive and Pig, we have a higher level abstraction. So it's much more easy for someone to use without having to dive in deep and write a very lengthy MapReduce code. And those map and reduce codes can take 70, 80 lines of code when you can do the same thing in 1 or 2 lines with Hive or Pig. This is the advantage Pig has over Hive. It can process only structured data in Hive, while in Pig it can process structured, semi-structured, and unstructured data. Some other features to note that separates the different query languages is when we look at map and reduce, MapReduce supports partitioning features, as does Hive. Pig, no concept of partitioning in Pig, so it doesn't support your partitioning feature. Your partitioning features allow you to partition the data in such a way that it can be queried quicker. You're not able to do that in Pig. MapReduce uses Java and Python, while Hive uses an SQL-like query language known as HiveQL or HQL. Pig Latin is used, which is a procedural data flow language. MapReduce is used by programmers, pretty much as straightforward on Java. Hive is used by data analysts. Pig is used by researchers and programmers. Certainly there's a lot of mix between all three. Programmers have been known to go in and use a Hive for a quick query, and anybody's been able to use Pig for a quick query or research. Under MapReduce, code performance is really good. Under Hive, code performance is lesser than MapReduce and Pig. Under Pig, code performance is lesser than MapReduce, but better than Hive. So if we're going to look at speed and time, the MapReduce is going to be the fastest performance on all of those, where Pig will have second and Hive follows in the back. Let's look at components of Pig. Pig has two main components. We have Pig Latin. Pig Latin is the procedural data flow language used in Pig to analyze data. It is easy to program using Pig Latin. It is similar to SQL. And then we have the runtime engine. Runtime engine represents the execution environment created to run Pig Latin programs. It is also a compiler that produces MapReduce programs. It uses HDFS, or your Hadoop file system, for storing and retrieving data. And as we dig deeper into the Pig architecture, we'll see that we have Pig Latin scripts. Programmers write a script in Pig Latin to analyze data using Pig. Then you have the grunt shell, and it actually says grunt when we start it up, and we'll show you that here in a little bit, which goes into the Pig server, and this is where we have our parser. Parser checks the syntax of the Pig script. After checking the output will be a DAG, directed acyclic graph. And then we have an optimizer, which optimizes after your DAG, your logical plan is passed to the logical optimizer where an optimization takes place. Finally, the compiler converts the DAG into MapReduce jobs, and then that is executed on the MapReduce under the execution engine. The results are displayed using dump statement and stored in HDFS using store statement. And again, we'll show you that. They kind of end, you always want to execute everything once you've created it, and so dump is kind of our execution statement. And you can see right here, as we were talking about earlier, once we get to the execution engine and it's coded into MapReduce, then the MapReduce processes it onto the HDFS. Working of Pig. Pig Latin script is written by the users. So you have load data and write Pig script and Pig operations. So when we look at the working of Pig, Pig Latin script is written by the users. There's step one. We load data and write Pig script. And step two, in this step, all the Pig operations are performed by parser, optimizer, and compiler. So we go into the Pig operations. And then we get to step three, execution of the plan. In this stage, the results are shown on the screen, otherwise stored in the HDFS as per the code. So it might be you have a small amount of data you're reducing it to and you want to put that on the screen, or you might be converting a huge amount of data which you want to put back into the Hadoop file system for other use. Let's take a look at the Pig Latin data model. The data model of Pig Latin helps Pig to handle various types of data. For example, we have Atom, Rob, or 50. Atom represents any single value of primitive data type in Pig Latin, like integer, float, string. It is stored as a string. Tuple, so we go from our atom, which are our most basic thing. So if you look at just Rob or just 50, that's an atom. That's our most basic object we have in Pig Latin. Then you have a tuple. Tuple represents sequence of fields that can be of any data type. It is the same as a row in RDBMS. For example, a set of data from a single row. And you can see here we have Rob, 5. And you can imagine with many of our other examples we've used, you might have the ID number, the name, where they live, their age, their date of starting the job. That would all be one row and stored as a tuple. And then we create a bag. A bag is a collection of tuples. It is the same as a table in RDBMS and is represented by brackets. And you can see here we have our table with Rob 5, Mike 10. And we also have a map. A map is a set of key value pairs. Key is of character array type and a value can be of any type. It is represented by the brackets. And so we have name and age, where the key value is Mike and 10. Pig Latin has a fully nestable data model. That means one data type can be nested within another. Here's a diagram representation of Pig Latin data model. And in this particular example, we have basically an ID number, a name, an age, and a place. And we break this apart. We look at this model from Pig Latin perspective. We start with our field. And if you remember, a field contains basically an atom. It is one particular data type, and the atom is stored as a string, which it then converts it into either an integer, number, or character string. Next we have our tuple, and in this case you can see that it represents a row. So our tuple would be 3, Joe, 29, California. And finally we have our bag, which contains 3 rows in it in this particular example. Let's take a quick look at pig execution modes. Pig works in 2 execution modes, depending on where the data is residing and where the pig script is going to run. We have local mode. Here the pig engine takes input from the Linux file system and the output is stored in the same file system. Local mode is useful in analyzing small datasets using pig. And we have the MapReduce mode. Here the pig engine directly interacts and executes in HDFS and MapReduce. In the MapReduce mode, queries written in pig Latin are translated into MapReduce jobs and are run on a Hadoop cluster. By default, pig runs in this mode. There are 3 modes in pig, depending on how a pig Latin code can be written. We have our interactive mode, batch mode, and embedded mode. The interactive mode means coding and executing the script line by line. When we do our example, we'll be in the interactive mode. In batch mode, all scripts are coded in a file with the extension .pig, and the file is directly executed. And then there's embedded mode. Pig lets its users define their own functions, UDFSs, in a programming language such as Java. So let's take a look and see how this works in a use case. In this case, use case Twitter. Users on Twitter generate about 500 million tweets on a daily basis. The Hadoop MapReduce was used to process and analyze this data. Analyzing the number of tweets created by a user in the tweet table was done using MapReduce in Java programming language. And you can see the problem. It was difficult to perform MapReduce operations as users were not well versed with written complex Java codes. So Twitter used Apache Pig to overcome these problems. And let's see how. Let's start with the problem statement. Analyze the user table and tweet table and find out how many tweets are created by a person. And here you can see we have a user table. We have Alice, Tim, and John with their ID numbers 1, 2, 3, and we have a tweet table. In the tweet table you have your the ID of the user and then what they tweeted. Google was a good whatever it was, tennis, spacecraft, Olympics, politics, whatever they're tweeting about. The following operations were performed for analyzing given data. First, the Twitter data is loaded into the pig storage using load command. And you can see here we have our data coming in and then that's going into pig storage. And this data is probably on an enterprise computer. So this is actually active Twitters going on and then it goes into Hadoop file system. Remember, the Hadoop file system is a data warehouse for storing data. And so the first step is we want to go ahead and load it into the pig storage, into our data storage system. The remaining operations performed are shown below. In join and group operation, the tweet and user tables are joined and grouped using cogroup command. And you can see here where we add a whole column when we go from usernames and tweet to the ID linked directly to the name. So Alice was user 1, Tim was 2, and John 3. And so now they're listed with their actual tweet. The next operation is the aggregation. The tweets are counted according to the names. The command used is count. So it's very straightforward. We just want to count how many tweets each user is doing. And finally, the result after the count operation is joined with the user table to find out the username. And you can see here where Alice had 3, Tim 2, and John 1. Pig reduces the complexity of the operations, which would have been lengthy using MapReduce. In join and group operation, the tweet and user tables are joined and grouped using cogroup command. The next operation is the aggregation. The tweets are counted according to the names. The command used is count. The result after the count operation is joined with the user table to find out the username. And you can see we're talking about 3 lines of script versus a MapReduce code of about 80 lines. Finally, we could find out the number of tweets created by a user in a simple way. So let's go quickly over some of the features of Pig that we already went through most of these. First, ease of programming, as Pig Latin is similar to SQL. Lesser lines of code need to be written. Short development time as the code is simpler, so we can get our queries out rather quickly instead of having to have a programmer spend hours on it. Handles all kind of data like structured, semi-structured, and unstructured. Pig lets us create user-defined functions. Pig offers a large set of operators such as join, filter, and so on. It allows for multiple queries to process in parallel, and optimization and compilation is easy as it is done automatically and internally. So enough theory. Let's dive in and show you a quick demo on some of the commands you can do in Pig. Today's setup will continue as we have in the last 3 demos to go ahead and use Cloudera Quick Start. And we'll be doing this in VirtualBox. We do have a tutorial in setting that up. You can send a note to our Simplilearn team and then get that link to you. Once your Cloudera Quick Start has spun up, and remember this is VirtualBox. We've created a virtual machine, and this virtual machine is CentOS Linux. Once it's spun up, you'll be in a full Linux system here. And as you can see, we have Thunderbird browser, which opens up to the Hadoop basic system browser. And we can go underneath the hue, where it comes up by default. If you click on the pull down menu and go under editor, you can see there's our Impala, our Hive, Pig, along with a bunch of other query languages you can use. And we're going under Pig. And then once you're in Pig, we can go ahead and use our command line here and just click that little blue button to start it up and running. We will actually be working in terminal window. And so if you're in the Cloudera Quick Start, you can open up the terminal window up top, or if you're in your own setup and you're logged in, you can easily use all of your commands here in terminal window. And we'll zoom in. That way you get a nice view of what's going on. There we go. Now for our first command, we're going to go ahead and do a Hadoop command and import some data into the Hadoop system, in this case a Pig input. And let's just take a look at this. We have Hadoop. Now let's know it's going to be a Hadoop command. DFS. There's actually 4 variations of DFS. So if you have HDFS or whatever, that's fine. All 4 of them used to be different setups underneath different things, and now they all do the same thing. And we want to put this file, which in this case is under Home Cloudera Documents and Sample, and we just want to take that and put it into the Pig input. And let's take a look at that file. If I go under my document browsers and open this up, you'll see it's got a simple ID, name, profession, and age. We have one Jack Engineer 25. And that was in one of our earlier things we had in there. And so let's go ahead and hit enter and execute this. And now we've uploaded that data and it's gone into our Pig input. And then a lot of the Hadoop commands mimic the Linux commands. And so you'll see we have cat as one of our commands, or it has a hyphen before it. So we execute that with Hadoop DFS -cat /pig input, because that's what we called it. That's where we put our sample CSV at. And we execute this. You can see from our Hadoop system, it's going to go in and pull that up. And sure enough, it pulls out the data file we just put in there. And then we can simply enter the Pig Latin or Pig editor mode by typing in Pig. And we can see here by our grunt, I told you that's how it was going to tell you were in Pig Latin. There's our grunt command line. So we are now in the Pig shell. And then we'll go ahead and put our load command in here. And the way this works is I'm going to have office equals load. And here's my load. In this case, it's going to be Pig input. We have that in single brackets. You remember that's where the data is in the Hadoop file system where we dumped it into there. We're going to be using Pig storage. Our data was separated as with a comma. So there's our comma separator. And then we have as. And in this case, we have an ID, character array, name, character array, profession, character array, and age, character array. And we're just going to do them all as character arrays just to keep this simple for this one. And then when I hit put this all in here, you can see that's our full command line going in. And we have our semicolon at the end. So when I hit enter, it's now set office up. But it hasn't actually done anything yet. It doesn't do anything until we do dump office. So there's our command to execute whatever we've loaded or whatever setup we have in here. And we run that. You can see it go through the different languages, and this is going through the MapReduce. Remember, we're not doing this locally, we're doing this on the Hadoop setup. And once we finished our dump, you can see we have ID, name, profession, age, and all the information that we just dumped into our Pig. We can now do, let's say we have a request just for, we'll keep it simple in here, but just for the name and age. And so we can go office, we'll call it each as our variable, underscore each, and we'll say for each office, generate name, comma, age. And for each means that we're going to do this for each row. And if you're thinking MapReduce, you know that this is a map function because it's mapping each row and generating name and age on here. And of course, we want to go ahead and close it with a semicolon. And then once we've created our query or the command line in here, let's go ahead and dump office underscore each, and with our semicolon. And this will go through our MapReduce setup on here. And if we were on a large cluster, the same processing time would happen. In fact, it's really slow because I have multiple things on this computer, and this particular virtual box is only using a quarter of my processor. It's only dedicated to this. And you can see here, there it is, name and age. And it also included the top row since we didn't delete that out of there or tell it not to. And that's fine for this example, but you need to be aware of those things when you're processing a significantly large amount of data or any data. Then we can also do Office, and we'll call this DSC for descending. So maybe the boss comes to you and says, hey, can we order Office by ID descending? And of course your boss, you've taught him how to, your shareholder, it sounds a little derogatory when I say boss. You've talked to the shareholder and you said, and you've taught them a little bit of Pig Latin, and they know that they can now create Office description, and we can order Office by ID description. And of course once we do that, we have to dump Office underscore description so that it'll actually execute, and there goes into our MapReduce. It'll take just a moment for it to come up because again I'm running on only a quarter of my processor, and you can see we now have our IDs in descending order returned. Let's also look at, and this is so important with anytime you're dealing with big data, let's create Office with a limit. And you could of course do any of this instead of with Office. We could do this with Office descending, so you get just the top 2 IDs on there. But we're going to limit just to 2, and of course to execute that we have to dump Office underscore limit. And you can just think of dumping your garbage into the pig pen for the pig to eat. There we go, dump Office limit 2, and that's going to just limit our Office to the top 2. And for our output we get our first row, which had our ID, name, profession, and age, and our second row, which is Jack, who's an engineer. And let's do a filter. We'll call it Office underscore filter. You guessed it, equals filter Office by profession equals, and keep note this is similar to how Python does it with the double equal signs for equal for doing a true false statement. So for your logic statement, remember to use 2 equal signs in pig, and we're going to say it equals doctor. So we want to find out how many doctors do we have on our list. And we'll go ahead and do our dump. We're dumping all our garbage into the pig pen, and we're letting pig take over and see what it can find out and see who's a doctor on our list. And we find employee ID number 2, Bob, is a doctor, 30 years old. For this next section, we're going to cover something we see a lot nowadays in data analysis, and that's word counting, tokenization. That is one of the next big steps as we move forward in our data analysis, where we go from, say, stock market analysis of highs and lows and all the numbers to what are people saying about companies on Twitter? What are they saying on the web pages and on Facebook? Suddenly you need to start counting words and finding out how many words are total, how many are in the first part of the document, and so on. We're going to cover a very basic word count example. And in this case, I've created a document called wordrows.txt. And you can see here we have Simplilearn is a company supporting online learning. Simplilearn helps people attain their certifications. Simplilearn is an online community. I love Simplilearn. I love programming. I love data analysis. And I went and saved this into my documents folder so we could use it. And let me go ahead and open up a new terminal window for our word count. Let me go ahead and close the old one. So we're going to go in here, and instead of doing this as pig, we're going to do pig -x local. And what I'm doing is I'm telling the pig to start the pig shell, but we're going to be looking at files local to our virtual box or this CentOS machine. And let me go ahead and hit enter on there. Just maximize this up. There we go. And it'll load pig up, and it's going to look just the same as the pig we were doing, which was defaulted to our Hadoop system, to our HDFS. This is now defaulted to the local system. And now we're going to create lines, and we're going to load it straight from the file. Remember last time we took the HDFS and loaded it into there and then loaded it into pig. Since we're on the local, we're just going to run a local script. We have lines equals load home, the actual full path, home, Cloudera, documents, and I called it wordrows.txt. And as line is a character array, so each line, and you can change this to read each document. I certainly have done a lot of document analysis, and then you go through and do word counts and different kind of counts in there. So once we go ahead and create our line, instead of doing the dump, we're going to go ahead and start entering all of our different setups for each of our steps we want to go through. And let's just take a look at this next one, because the load is straightforward. We're loading from this particular file. Since we're local, it's loading it directly from here instead of going into the Hadoop file system. And it says as, and then each line is read as a character array. Now we're going to do words equal for each of the lines, generate flat tokenize line space as word. Now there's a lot of ways to do this. This is if you're a programmer, you're just splitting the line up by spaces. There's actual ways to tokenize it. You gotta look for periods, capitalization. There's all kinds of other things you play with this. But for the most basic word count, we're just going to separate it by spaces. The flatten takes the line and just creates it flattens each of the words out. So this is, we're just going to generate a bunch of words for each line. And then each of those words is as a word. A little confusing in there, but if you really think about it, we're just going down each line, separating it out, and we're generating a list of words. One thing to note is the default for tokenize. You can just do tokenize line without the space in there. If you do that, it'll automatically tokenize it by space. You can do either one. And then we're going to do group. We're going to group it by words. So we're going to group words by word. So when we split it up, each token is a word and it's a list of words. And so we're going to grouped equals group words by word. So we're going to group all the same words together. And if we're going to group them, then we want to go ahead and count them. And so for count, we'll go ahead and create a word count variable. And here's our for each. So for each grouped is our line where we group all the words in the line that are similar. We're going to generate a group. And then we're going to count the words. For each grouped, so for each line where we group the words together, we're going to generate a group, and that's going to count the words. So we want to know the word count in each of those. And that comes back in our word count. And finally, we want to take this and we want to go ahead and dump word count. And this is a little bit more what you see when you start looking at grunt scripts. You'll see right here, these lines right here, we have each of the steps you take to get there. So we load our file. For each of our lines, we're going to generate and tokenize it into words. Then we're going to take the words and we're going to group them by same words. For each grouped, we're going to generate a group and we're just going to count the words. So we're going to summarize all the words in here. And let's go ahead and do our dump word count, which executes all this. And it goes through our MapReduce. It's actually a local runner. You'll see down here, you start seeing where they still have MapReduce, but it's a special runner. We're mapping it. That's a part of each row being counted and grouped. And then when we do the word count, that's the reducer. The reducer creates these keys. And you can see I is used 3 times, A came up once, and came up once, is 2. You can continue on down here to attain, online, people, company, analysis. Simplilearn, they took the top rating with 4. Certification. So all these things are then counted in the how many words are used. And in data analysis, this is probably the beginnings of data analysis, where you might look at it and say, oh, they mentioned love 3 times. So whatever's going on in this post, it's about love. And what do they love? And then you might attach that to the different objects in here. So you can see that Pig Latin is fairly easy to use. There's nothing really, it takes a little bit to learn the script. Depending on how good your memory is. As I get older, my memory leaks a little bit more, so I don't memorize it as much. But that was pretty straightforward, the script we put in there. And then it goes through the full MapReduce localized run, comes out, and like I said, it's very easy to use. That's why people like Pig Latin, is because it's intuitive. One of the things I like about Pig Latin is when I'm troubleshooting. When we're troubleshooting, a lot of times you're working with a small amount of data, and you start doing one line at a time, and so I can go lines equal load, and there's my loaded text, and maybe I'll just dump lines. And then it's going to run, it's going to show me all the lines that I'm working on in this small amount of data. And that way I can test that. If I got an error on there that said, oh, this isn't working, maybe I'll be like, oh my gosh, I'm in MapReduce, or I'm in the basic grunt shell instead of the local path grunt. Let's start with an introduction to HBase. Back in the days, data used to be less and was mostly structured. You can see we have structured data here. We usually had it like in a database where you had every field was exactly the correct length. So if you had a name field, it was exactly 32 characters. I remember the old Access database in Microsoft. The files were small. If we had hundreds of people in one database, that was considered big data. This data could be easily stored in relational database, or RDBMS. When we talk about relational database, you might think of Oracle, you might think of SQL, Microsoft SQL, MySQL. All of these have evolved even from back then to do a lot more today than they did. But they still fall short in a lot of ways. And they're all examples of an RDMS or relationship database. Then internet evolved and huge volumes of structured and semi-structured data got generated. And you can see here with the semi-structured data, we have email. If you look at my spam folder, you know what we're talking about. All the HTML pages, XML, which is a lot of times is displayed on our HTML and help desk pages, JSON. All of this really has just, even in the last, each year it almost doubles from the year before how much of this is generated. So storing and processing this data on an RDBMS has become a major problem. And so the solution is we use Apache HBase. Apache HBase was the solution for this. Let's take a look at the history, the HBase history. And we look at the HBase history. We're going to start back in 2006, November. Google released a paper on Big Table. And then in 2017, just a few months later, HBase prototype was created as a Hadoop contribution. Later on in the year 2007, in October, first usable HBase along with the Hadoop 0.15 was released. And then in January of 2008, HBase became the subproject of Hadoop. And later on that year in October, all the way into September the next year, HBase was released, the 0.81 version, the 0.19 version, and 0.20. And finally, in May of 2010, HBase became Apache top-level project. And so you can see in the course of about 4 years, HBase started off as just an idea on paper and has evolved all the way till 2010 as a solid project under the Apache. And since 2010, it's continued to evolve and grow as a major source for storing data in semi-structured data. So what is HBase? HBase is a column-oriented database management system derived from Google's NoSQL database, Big Table, that runs on top of the Hadoop file system, or the HDFS. It's an open source project that is horizontally scalable, and that's very important to understand, that you don't have to buy a bunch of huge expensive computers. You're expanding it by continually adding commodity machines. And so it's a linear cost expansion as opposed to being exponential. NoSQL database written in Java, which permits faster querying. So Java is the backend for the HBase setup. And it's well suited for sparse datasets. So it can contain missing or NA values, and this doesn't boggle it down like it would another database. Companies using HBase. So let's take a look and see who is using this NoSQL database for their servers and for storing their data. And we have Hortonworks, which isn't a surprise because they're one of the, like Cloudera, Hortonworks. They are behind Hadoop and one of the big developments and backing of it. And of course, Apache HBase is the open source behind it. And we have Capital One as banks. You also see Bank of America, where they're collecting information on people and tracking it. So their information might be very sparse. They might have one bank way back when they collected information as far as the person's family and what their income for the whole family is and their personal income, and maybe another one doesn't collect the family income. As you start seeing where you have data that is very difficult to store, where it's missing a bunch of data. HubSpot's using it, Facebook, certainly all of your Facebook, Twitter, most of your social medias are using it. And then of course there's JP Morgan, Chase and Company, another bank that uses the HBase as their data warehouse for NoSQL. Let's take a look at an HBase use case so we can dig a little bit more into it to see how it functions. Telecommunication company that provides mobile voice and multimedia services across China, the China Mobile. And China Mobile, they generate billions of call detailed records, or CDR. And so these CDRs and all these records of these calls and how long they are and different aspects of the call, maybe the tower they're broadcasted from, all of that is being recorded so they can track it. Traditional database systems were unable to scale up to the vast volumes of data and provide a cost-effective solution. No good. So storing and real-time analysis of billions of call records was a major problem for this company. Solution? Apache HBase. HBase stores billions of rows of detailed call records. HBase performs fast processing of records using SQL queries. So you can mix your SQL and NoSQL queries. And usually just say NoSQL queries because of the way the query works. Applications of HBase. One of them would be in the medical industry. HBase is used for storing genome sequences, storing disease history of people of an area, and you can imagine how sparse that is as far as both of those. A genome sequence might only have pieces to it that each person is unique or is unique to different people. And the same thing with disease. You really don't need a column for every possible disease a person could get. You just want to know what those diseases those people have had to deal with in that area. E-commerce. HBase is used for storing logs about customer search history, performs analytics and target advertisement for better business insights. Sports. HBase stores match details and the history of each match. Uses this data for better prediction. So when we look at HBase, we all want to know what's the difference between HBase versus RDBMS. That is a relational database management system. HBase versus RDBMS. So the HBase does not have a fixed schema. It's schemaless. Defines only column families. And we'll show you what that means later on. An RDBMS has a fixed schema which describes the structure of the tables. And you can think of this as you have a row and you have columns. And each column is a very specific structure, how much data can go in there and what it does. With the HBase, it works well with structured and semi-structured data. With the RDBMS, it works only well with structured data. With the HBase, it can have denormalized data. It can contain missing or null values. With the RDBMS, it can store only normalized data. Now you can still store a null value in the RDBMS, but it still takes up the same space as if you're storing a regular value in many cases. And it also, for the HBase, is built for wide tables. It can be scaled horizontally. For instance, if you were doing a tokenizer of words and word clusters, you might have 1.4 million different words that you're pulling up and combinations of words. So with an RDBMS, it's built for thin tables that are hard to scale. You don't want to store 1.4 million columns in your SQL. It's going to crash and it's going to be very hard to do searches. With the HBase, it only stores that data which is part of whatever row you're working on. Let's look at some of the features of the HBase. It's scalable. Data can be scaled across various nodes as it is stored in the HDFS. And I always think about this, it's a linear add-on. For each terabyte of data, I'm adding on roughly $1,000 in commodity computing. With an enterprise machine, we're looking at about $10,000 at the lower end for each terabyte of data. And that includes all your backup and redundancy. So it's a big difference. It's like a tenth of the cost to store it across the HBase. It has automatic failure support. Write-ahead log across clusters, which provides automatic support against failure. Consistent read and write. HBase provides consistent read and write of the data. It's a Java API for client access. Provides easy to use Java API for clients. Block cache and bloom filters. So the HBase supports block caching and bloom filters for high volume query optimization. Let's dig a little deeper into the HBase storage. HBase column oriented storage. And I told you we're going to look into this to see how it stores the data. And here you can see you have a row key. And this is really one of the important references is each row has to have its own key or your row ID. And then you have your column family. And in here you can see we have column family 1, column family 2, column family 3. And you have your column qualifiers. So you can have in column family 1, you can have 3 columns in there, and there might not be any data in that. So when you go into column family 1 and do a query for every column that contains a certain thing, that row might not have anything in there and not be queried. Where in column family 2, maybe you have column 1 filled out and column 3 filled out, and so on and so forth. And then each cell is connected to the row where the data is actually stored. Let's take a look at this and what it looks like when you fill the data in. So in here we have a row key with a row ID, and we have our employee ID, 1, 2, 3. That's pretty straightforward. You probably would even have that on an SQL server. And then you have your column family. This is where it starts really separating out. Your column family, you might have personal data, and under personal data you would have name, city, age. You might have a lot more than just that. You might have number of children, you might have degree, all those kinds of different things that go under personal data. And some of them might be missing. You might only have the name and the age of an employee. You might only have the name, the city, and how many children, and not the age. And so you can see with the personal data, you can now collect a large variety of data and store it in the HBase very easily. And then maybe you have a family of professional data, your designation, your salary, all the stuff that the employee is doing for you in that company. Let's dig a little deeper into the HBase architecture. And so you can see here what looks to be a complicated chart. It's not as complicated as you think. From the Apache HBase, we have the Zookeeper, which is used for monitoring what's going on. And you have your HMaster. This is the HBase master, assigns regions and load balancing. And then underneath the region, or the HBase master, then under the HMaster or HBase master, you have your region server serves data for read and write. And the region server, which is all your different computers you have in your Hadoop cluster, you'll have a region, an HLog, you'll have a store, memory store, and then you have your different files for HFile that are stored on there. And those are separated across the different computers. And that's all part of the HDFS storage system. So when we look at the architectural components or regions, and we're drilling down a little bit, HBase tables are divided horizontally by row. So you have a key range into regions. So each of those IDs, you might have IDs 1 to 20, 21 to 50, or whatever they are. Regions are assigned to the nodes in the cluster called region servers. A region contains all rows in the table between the region start key and the end key. Again, 1 to 10, 11 to 20, and so forth. These servers serve data for read and write. And you can see here we have the client and the get sends it out and it finds out where that start, if it's between which start keys and end keys, and then it pulls the data from that different region server. And so the region signed data definition language operation, create, delete, are handled by the HMaster. So the HMaster is telling it, what are we doing with this data? What's going out there? Assigning and reassigning regions for recovery or load balancing and monitoring all servers. So that's also part of it. So, if your IDs, if you have 500 IDs across 3 servers, you're not going to put 400 IDs on server 1 and 100 on the server 2 and leave region 3 and region 4 empty. You're going to split that up, and that's all handled by the HMaster. And you can see here it monitors region servers, assigns regions to region servers, assigns regions to region servers, and so forth and so forth. HBase has a distributed environment where HMaster alone is not sufficient to manage everything. Hence, Zookeeper was introduced. It works with HMaster. So you have an active HMaster which sends a heartbeat signal to Zookeeper indicating that it's active. And the Zookeeper also has a heartbeat to the region servers. So the region servers send their status to Zookeeper indicating they are ready for read and write operation. Inactive server acts as a backup. If the active HMaster fails, it will come to the rescue. Active HMaster and region servers connect with a session to Zookeeper. So you see your active HMaster selection, your region server session. They're all looking at the Zookeeper keeping that pulse. An active HMaster and region server connects with a session to the Zookeeper. And you can see here where we have ephemeral nodes for active sessions via heartbeats to indicate that the region servers are up and running. So let's take a look at HBase read or write going on. There's a special HBase catalog table called the meta table, which holds a location of the regions in the cluster. Here's what happens the first time a client reads or writes data to HBase. The client gets the region server, the host, the meta table from Zookeeper. And you can see right here the client has a request for your region server and goes, hey, Zookeeper, can you handle this? And the Zookeeper takes a look at it and goes, meta location is stored in Zookeeper. So it looks at its metadata on there. And then the metadata table location is sent back to the client. The client will query the meta server to get the region server corresponding to the row key if it wants to access. The client caches this information along with the metatable location. And you can see here the client going back and forth to the region server with the information. And it might be going across multiple region servers depending on what you're querying. So we get the region server for row key from the metatable. That's where that row key comes in and says, hey, this is where we're going with this. And so once it gets the row key from the corresponding region server, we can now put row or get row from that region server. Let's take a look at the HBase metatable. Special HBase catalog table that maintains a list of all the region servers in the HBase storage system. So you see here we have the metatable. We have a row key and a value, table key, region, region server. So the metatable is used to find the region for the given table key. And you can see down here, our metatable comes in, it's going to figure out where it's going with the region server. And when we look a little closer at the write mechanism in HBase, we have write ahead log, or WAL, as you abbreviate it. Kind of a way to remember WAL is write ahead log. It's a file used to store new data that is yet to be put on permanent storage. It is used for recovery in the case of failure. So you can see here where the client comes in and it literally puts the new data coming in into this kind of temporary storage or the WAL on there. Once it's gone into the wall, then the memory store, mem store, is a write cache that stores the new data that has not yet been written to disk. There is one mem store per column family per region. And once we've done that, we have 3 ACK. Once the data is placed in mem store, the client then receives the acknowledgement. When the mem store reaches the threshold, it dumps or commits the data into H file. And so you can see right here, we've taken it's gone into the wall then sorts it into the different memory stores, and then the memory stores, it says, hey, we're ready to dump that into our H files, and then it moves it into the H files. H files store the rows of data as stored key value on disk. So here we've done a lot of theory. Let's dive in and just take a look and see what some of these commands look like and what happens in our HBase when we're manipulating a NoSQL setup. So if you're learning a new setup, it's always good to start with, where is this coming from? It's open source by Apache. And you can go to hbase.apache.org. And you'll see that it has a lot of information. You can actually download the HBase separate from the Hadoop, although most people just install the Hadoop because it's bundled with it. And if you go in here, you'll find a reference guide. And so you can go through the Apache reference guide. And there's a number of things to look at, but we're going to be going through Apache HBase shell. That's what we're going to be working with. And there's a lot of other interfaces on the setup, and you can look up a lot of the different commands on here. So when we go into the Apache HBase reference guide, we can go down to read HBase shell commands from a command file. You can see here where it gives you different options of formats for putting the data in and listing the data. Certainly you can also create files and scripts to do this too. But we're going to look at the basics, and we're going to go through this on a basic HBase shell. And one last thing to look at is, of course, if you continue down the setup, you can see here where they have more detail as far as how to create and how to get to your data on your HBase. Now, I will be working in a virtual box, and this is by Oracle. You can download the Oracle VirtualBox. You can put a note in below for the YouTube, as we did have a previous session on setting up virtual setup to run your Hadoop system in there. I'm using the Cloudera Quick Start installed in here. There's Hortons. You can also use the Amazon Web Service. There's a number of options for trying this out. In this case, we have Cloudera on the Oracle VirtualBox. The VirtualBox has Linux CentOS installed on it, and then the Hadoop has all the different Hadoop flavors, including HBase. And I bring this up because my computer is a Windows 10. The operating system of the VirtualBox is Linux, and we're looking at the HBase data warehouse. And so we have 3 very different entities all running on my computer. And that can be confusing if it's the first time in and working with this kind of setup. Now, you'll notice in our Cloudera setup, they actually have some HBase monitoring. So I can go underneath here and click on HBase and master, and it'll tell me what's going on with my region servers. It'll tell me what's going on with our backup tables. Right now I don't have any user tables because we haven't created any. And this is only a single node and a single HBase store. So you're not going to expect anything too extensive in here, since this is for practice and education and perhaps testing out package you're working on. It's not for really, you can deploy Cloudera, of course, but when you talk about a quick start or a single node setup, that's what it's really for. So we can go through all the different HBase, and you'll see all kinds of different information with Zookeeper, if you saw it flash by down here, what version we're working in, since Zookeeper is part of the HBase setup. Where we want to go is we want to open up a terminal window, and in Cloudera it happens to be up at the top. And when you click on here, you'll see your Cloudera terminal window open. And let me just expand this so we have a nice full screen. And then I'm also going to zoom in. That way you have a nice big picture and you can see what I'm typing and what's going on. And to open up your HBase shell, simply type HBase shell to get in and hit enter. And you'll see it takes just a moment to load, and we'll be in our HBase shell for doing HBase commands. Once we've gotten into our HBase shell, you'll see it'll have the HBase prompt information ahead of it. We can do something simple like list. And this is going to list whatever tables we have. And it so happens that there's a base table that comes with HBase. Now we can go ahead and create, and I'm going to type in just create. What's nice about this is it's going to throw me kind kind of a, it's going to say, hey, there's no just straight create. But it does come up and tell me all these different formats we can use for create. So we can create our table and one of our families. You can add splits, names, versions, all kinds of things you can do with this. But let's just start with a very basic one on here. And let's go ahead and create, and we'll call it new table. Let's just call it new TBL for table. New table. And then we also want to do, let's do knowledge. So let's take a look at this. I'm creating a new table, and it's going to have a family of knowledge in it. And let me hit enter. And it's going to come up. It's going to take it a second to go ahead and create it. Now we have our new table in here. And so if I go list, you'll now see table and new table. So you can now see that we have the new table and of course the default table that's set up in here. And we can do something like describe. We can describe, and then we're going to do new TBL. And when we describe it, it's going to come up. It's going to say, hey, name, I have knowledge, data block encoding none, Bloom filter, row, replication scope, version, all the different information you need. New, minimum version, 0, forever, deleted cells, false, block size, in memory. And you can look this stuff up on apache.org to really track it down. One of the things that's important to note is versions. So you have your different versions of the data that's stored. And that's always important to understand that. We might talk about that a little bit later on. And then after we describe it, we can also do a status. The status says I have one active master going on. That's our HBase as a whole. We can do status summary. That should do the same thing as status. So we got the same thing coming up. And now that we've created, let's go ahead and put something in it. So we're going to put new TBL, and then we want row 1. You know what, before I even do this, let's just type in put. And you can see when I type in put, it gives us like a lot of different options of how it works and different ways of formatting our data as it goes in. And all of them usually begin with the new table, new TBL. Then we have, in this case, we'll call it row 1, and then we'll have knowledge. If you remember, we created knowledge already, and we'll do knowledge sports. And then in knowledge and sports, we're going to set that equal to cricket. So we're going to put underneath this our knowledge setup. We have a thing called sports in there. And we'll see what this looks like in just a second. Let's go ahead and put in, we'll do a couple of these. Let's see, let's do another row 1, and this time instead of sports, let's do science. This person not only, we have row 1, which is both knowledgeable in cricket and also in chemistry. So it's a chemist who plays cricket in row 1. And let's see, if we have, let's do another row 1 just to keep it going. And we'll do science. In this case, let's do physics. Not only in chemistry, but also a physicist. I have quite a joy in physics myself. So here we go. We have row 1. There we go. And then let's do row 2. Let's see what that looks like when we start putting in row 2. And in row 2, this person has knowledge in economics. This is a master of business and how, or maybe it's global economics. Maybe it's just for the business and how it fits in with the country's economics. And we'll call it macroeconomics. So I guess it is for the whole country there. So we have knowledge economics, macroeconomics. And then let's just do one more. We'll keep it as row 2. And this time our economist is also a musician. So we'll put music. And they happen to have knowledge and they enjoy, let's do pop music. They're into the current pop music going on. So we've loaded our database. And you'll see we have 2 rows, row 1 and row 2 in here. And we can do is we can list the contents of our database by simply doing scan. Scan, and then let's just do scan by itself so you can see how that looks. You can always just type in there and it tells you all the different setups you can do with scan and how it works. In this case, we want to do scan new TBL. And in our scan new TBL, we have row 1, row 1, row 2, row 2. And you'll see row 1 has a column called knowledge, science, time step, value crickets, value physics. So it has information as when it was created, when the timestamp is. Row 1 also has knowledge sports and a value of cricket. So we have sports and science. And this is interesting because if you remember up here, we also gave it originally, we told it to come in here and have chemistry. We had science, chemistry, and science physics. And we come down here, I don't see the chemistry. Why? Because we've now replaced chemistry with physics. And so the new value is physics on here. Let me go ahead and clear down a little bit. And in this, we're going to ask the question, is enabled new new table. And when I hit enter in here, you're going to see it comes out true. And then we'll go ahead and disable it. Let's go ahead and disable new table. Make sure I have our quotes around it. And now that we've disabled it, what happens when we do the scan? When we do the scan new table, and I hit enter, you're going to see that we get an error coming up. So once it's disabled, you can't do anything with it until we re-enable it. Now, before we enable the table, let's do an alteration on it. And here's our new table. And this should look a little familiar because it's very similar to create. We'll call this test info. And we'll hit enter in there. It'll take just a moment for updating. And then we want to go ahead and enable it. So let's go ahead and enable our new table. So it's back up and running. And then we want to describe. Describe new table. And we come in here, you'll now see we have name knowledge. And under there we have our data encoding and all the information under knowledge. And then we also have down below test info. So now we have the name test info and all the information concerning the test info on here. And we'll simply enable it. New table. So now it's enabled. Oops, I already did that. I guess we'll enable it twice. And so let's start looking at, well, we had scan new table. And you can see here where it brings up the information like this. But what if we want to go ahead and get a row? So we'll do R1. And when we do HBase R1, you can see we have knowledge science and it has a timestamp, value physics, and we have knowledge sports and it has a timestamp on it, and value cricket. And then let's see what happens when we put into our new table, and in here we want row 1. And if you can guess from earlier, because we did something similar, we're going to do knowledge economics, and then it's going to be, instead of I think it was macroeconomics, it's now market economics. And we'll go back and do our get command and now see what it looks like. And we can see here where we have knowledge economics, it has a timestamp, value, market economics, physics, and cricket. And this is because we have economics, science, and sports. Those are the 3 different columns that we have, and then each one has different information in it. And so if you manage to go through all these commands and look at basics on here, you'll now have the ability to create a very basic HBase setup, no SQL setup, based on your columns and your rows.
Thank you guys. Now that we're done with Hadoop ecosystem, we have Shruti who will take us through big data applications.
Before we move on to the applications, let's have a quick look at the big data market revenue forecast worldwide from 2011 to 2027. So here's a graph in which the y-axis represents the revenue in billion US dollars and the x-axis represents the years. As it is seen clearly from the graph, big data has grown until 2019 and statistics predict that this growth will continue even in the future. This growth is made possible as numerous companies use big data in various domains to boost their revenue. We will look into a few of such applications. The first big data application we will look into is weather forecast. Imagine there is a sudden storm and you're not even prepared. That would be a terrifying situation, isn't it? Dealing with any calamities such as hurricanes, storms, floods would be very inconvenient if we are caught off guard. The solution is to have a tool that predicts the weather of the coming days well in advance. This tool needs to be accurate, and to make such a tool, big data is used. So how does big data help here? Well, it allows us to gather all the information required to predict the weather. Information such as the climate change details, wind direction, precipitation, previous weather reports, and so on. After all this data is collected, it becomes easier for us to spot a trend and identify what's going to happen next by analyzing all of this big data. A weather prediction engine works on this analysis. It predicts the weather of every region across the world for any given time. By using such a tool, we can be well prepared to face any climate change or any natural calamity. Let's take an example of a landslide and try to understand how big data is used to tackle such a situation. Predicting a landslide is very difficult with just the basic warning signs. Lack of this prediction can cause a huge damage to life and property. This challenge was studied by the University of Melbourne, and they developed a tool which is capable of predicting a landslide. This tool predicts the boundary where a landslide is likely to occur 2 weeks before. This magical tool works on both big data and applied mathematics. An accurate prediction like this, which is made 2 weeks before, can save lives and help in relocating people in that particular region. It also gives us an insight into the magnitude of the upcoming destruction. This is how big data is used in weather forecast and in predicting any natural calamities across the world. Let us now move on to our next application, that is big data application in the field of media and entertainment. The media and the entertainment industry is a massive one. Leveraging big data here can produce sky-high results and boost the revenue for any company. Let us see the different ways in which big data is used in this industry. Have you ever noticed that you come across relevant advertisements in your social media sites and in your mailboxes? Well, this is done by analyzing all your data such as your previous browsing history and your purchase data. Publishers then display what you like in the form of ads, which will in turn catch your interest in looking into it. Next up is customer sentiment analysis. Customers are very important for a company. The happier the customer, the greater the company's revenue. Big data helps in gathering all the emotions of a customer through their posts, messages, conversations, etc. These emotions are then analyzed to arrive at a conclusion regarding the customer's satisfaction. If the customer is unhappy, the company strives to do better the next time and provides their customers a better experience. While purchasing an item from an e-commerce site or while watching videos on an entertainment site, you might have noticed a segment which says most recommended list for you. This list is a personalized list which is made available to you by analyzing all the data such as your previous watch history, your subscriptions, your likes, and so on. Recommendation engine is a tool that filters and analyzes all this data and provides you with a list that you would most likely be interested in. By doing so, the site is able to retain and engage its customer for a longer time. Next is customer churn analysis. In simple words, customer churn happens when a customer stops their subscription with a service. Predicting and preventing this is of paramount importance to any organization. By analyzing the behavioral patterns of previously churned customers, an organization can identify which of their current customers are likely to churn. By analyzing all of this data, the organization can then implement effective programs for customer retention. Let us now look into an use case of Starbucks. Big data is effectively used by the Starbucks app. 17 million users use this app, and you can imagine how much data they generate. Data in the form of their coffee buying habits, the store they visit, and to the time they purchase. All of this data is fed into the app. So when a customer enters a new Starbucks location, the system analyzes all their data and they are provided with their preferred order. This app also suggests new products to the customer. In addition to this, they also provide personalized offer and discounts on special occasions. Moving on to our next sector, which is healthcare. It is one of the most important sectors. Big data is widely used here to save lives. With all the available big data, medical researches are done very effectively. They are performed accurately by analyzing all the previous medical histories, and new treatments and medicines are discovered. Cure can be found out even for few of the incurable diseases. There are cases when one medication need not be effective for every patient. Hence, personal care is very important. Personal care is provided to each patient depending on their past medical history. An individual's medical history along with their body parameters are analyzed, and personal attention is given to each of them. As we all know, medical treatments are not very pocket friendly. Every time a medical treatment is taken, the amount increases. This can be reduced if readmissions are brought down. Analyzing all the data precisely will deliver a long-term efficient result, which will in turn prevent a patient's readmission frequently. With globalization came an increase in the ease for infectious diseases to spread widely. Based on geography and demographics, big data helps in predicting where an outbreak of epidemic viruses are most likely to occur. An American healthcare company, United Healthcare, uses big data to detect any online medical fraud activities such as payment of unauthorized benefits, intentional misrepresentation of data, and so on. The healthcare company runs disease management programs. The success rates of these programs are predicted using big data depending on how patients respond to it. The next sector we will look into is logistics. Logistics looks into the process of transportation and storage of goods. The movement of a product from its supplier to a consumer is very important. Big data is used to make this process faster and efficient. The most important factor in logistics is the time taken for the products to reach their destination. To achieve minimum time, sensors within the vehicle analyze the fastest route. This analysis is based on various data such as the weather, traffic, the list of orders, and so on. By doing so, the fastest route is obtained and the delivery time is reduced. Capacity planning is another factor which needs to be taken into consideration. Details regarding the workforce and the number of vehicles are analyzed thoroughly, and each vehicle is allocated a different route. This is done as there is no need for many trucks to travel in the same direction, which will be pointless. Depending on the analysis of the available workforce and resources, this decision is taken. Big data analytics also finds its use in managing warehouses efficiently. This analysis, along with tracking sensors, provide information regarding the underutilized space, which results in efficient resource allocation and eventually reduces the cost. Customer satisfaction is important in logistics just like it is in any other sector. Customer reactions are analyzed from the available data, which will eventually create an instant feedback loop. A happy customer will always help the company gain more customers. Let us now look into a use case of UPS. As you know, UPS is one of the biggest shipping company in the world. They have a huge customer database and they work on data every minute. UPS uses big data to gather different kinds of data regarding the weather, the traffic jams, the geography, the locations, and so on. After collecting all this data, they analyze it to discover the best and the fastest route to the destination. In addition to this, they also use big data to change the routes in real time. This is how efficiently UPS leverages big data. Next up, we have a very interesting sector, that is the travel and tourism sector. The global tourism market is expected to grow in the near future. Big data is used in various ways in this sector. Let us look into a few of them. Hotels can increase their revenue by adjusting the room tariffs depending on the peak seasons, such as holiday seasons, festive seasons, and so on. The tourism industry uses all of this data to anticipate the demand and maximize their revenue. Big data is also used by resorts and hotels to analyze various details regarding their competitors. This analysis result helps them to incorporate all the good facilities their competitors are providing, and by doing so, the hotel is able to flourish further. A customer always comes back if they are offered good packages which are more than just the basic ones. Looking into a customer's past travel history, likes, and preferences, hotels can provide its customers with personalized experiences which will interest them highly. Investing in an area which could be the hub of tourism is very wise. Few countries use big data to examine the tourism activities in their country, and this in turn helps them discover new and fruitful investment opportunities. Let us look into one of the best online homestay networks, Airbnb, and see how big data is used by them. Airbnb undoubtedly provides its customers with the best accommodation across the world. Big data is used by it to analyze the different kinds of available properties. Depending on the customer's preferences, the pricing, the keywords, previous customers, ratings, and experiences, Airbnb filters out the best result. Big data works its magic yet again. Now we will move on to our final sector, which is the government and law enforcement sector. Maintaining law and order is of utmost importance to any government. It is a huge task by itself. Big data plays an active role here, and in addition to this, it also helps governments bring in new policies and schemes for the welfare of its citizens. The police department is able to predict criminal activities way before it happens by analyzing big data information such as the previous crime records in a particular region, the safety aspect in that region, and and so on. By analyzing these factors, they are able to predict any activity which breaks the law and order of the region. Governments are able to tackle unemployment to a great extent by using big data. By analyzing the number of students graduating every year to the number of relevant job openings, the government can have an idea of the unemployment rate in the country and then take necessary measures to tackle it. Our next factor is poverty. In large countries, it is difficult to analyze which area requires attention and development. Big data analytics makes it easier for governments to discover such areas. Poverty gradually decreases once these areas begin to develop. Governments have to always be on the lookout for better development. A public survey voices the opinion of a country's citizens. Analyzing all the data collected from such surveys can help governments build better policies and services which will benefit its citizens. Let us now move on to our use case. Did you know that the New York Police Department uses big data analytics to protect its citizens? The department prevents and identifies crimes by analyzing a huge amount of data, which includes fingerprints, certain emails, and records from previous police investigations, and so on. After analyzing all of this data, meaningful insights are drawn from it, which will help the police in taking the required preventive measures against crimes.
Thank you, Shruti. Let us now have a look at the next data processing framework, Spark. We have our instructor Ajay, who will take us through Apache Spark, its installation.
Welcome to this tutorial on Apache Spark, one of the most in-demand technologies and processing frameworks in the big data world. And here we will learn on Apache Spark, history of Spark, what is Spark, Hadoop, which is a framework again, WES Spark, components of Apache Spark, that is Spark Core, Spark SQL, Spark Streaming, Spark MLlib, and graphics. Then we will learn on Spark architecture, applications of Spark, Spark use cases. So let's begin with understanding about history of Apache Spark. It all started in 2009 as a project at UC Berkeley AMP Labs by Mate Zaharia. In 2010, it was open sourced under a BSD license. In 2013, Spark became an Apache top-level project, and in 2014, used by Databricks to sort large-scale datasets, and it set a new world record. So that's how Apache Spark started, and today it is one of the most in-demand processing framework, or I would say in-memory computing framework, which is used across the big data industry. So what is Apache Spark? Let's learn about this. Apache Spark is an open source in-memory computing framework, or you could say data processing engine, which is used to process data in batch and also in real time across various cluster computers. And it has a very simple programming language behind the scenes, that is Scala, which is used. Although if users would want to work on Spark, they can work with Python, they can work with Scala, they can work with Java, and so on, even R for that matter. So it supports all these programming languages, and that's one of the reasons that it is called polyglot, wherein you have good set of libraries and support from all the programming languages, and developers and data scientists incorporate Spark into their applications or build Spark-based applications to process, analyze, query, and transform data at a very large scale. So these are key features of Apache Spark. Now, if you compare Hadoop with Spark, we know that Hadoop is a framework, and it basically has MapReduce, which comes with Hadoop for processing data. However, processing data using MapReduce in Hadoop is quite slow because it is a batch-oriented operation and it is time-consuming. If you talk about Spark, Spark can process the same data 100 times faster than MapReduce, as it is a in-memory computing framework. Well, there can always be conflicting ideas saying, what if my Spark application is not really efficiently coded and my MapReduce application has been very efficiently coded? Well, then it's a different case. However, normally, if you talk about code which is efficiently written for MapReduce or for Spark-based processing, Spark will win the battle by doing almost 100 times faster than MapReduce. So as I mentioned, Hadoop performs batch processing, and that is one of the paradigms of MapReduce programming model, which involves mapping and reducing, and that's quite rigid. So it performs batch processing. The intermittent data is written to HDFS and read back from HDFS, and that makes Hadoop's MapReduce processing slower. In case of Spark, it can perform both batch and real-time processing. However, a lot of use cases are based on real-time processing. Take an example of Macy's, take an example of retail giant such as Walmart, and there are many use cases who would prefer to do real-time processing, or I would say near real-time processing. So when we say real-time or near real-time, it is about processing the data as it comes in, or you're talking about streaming kind of data. Now, Hadoop or Hadoop's MapReduce obviously was started to be written in Java. Now you could also write it in Scala or in Python. However, if you talk about MapReduce, it will have more lines of code since it is written in Java, and it will take more times to execute. You have to manage the dependencies, you have to do the right declarations, you have to create your mapper and reducer and driver classes. However, if you compare Spark, it has few lines of code as it is implemented in Scala, and Scala is a statically typed, dynamically inferred language. It's very, very concise, and the benefit is it has features from both functional programming and object-oriented language. And in case of Scala, whatever code is written, that is converted into byte codes, and then it runs in the JVM. Now, Hadoop supports Kerberos authentication. There are different kind of authentication mechanisms. Kerberos is one of the well-known ones, and it can really get difficult to manage. Now, Spark supports authentication via a shared secret. It can also run on Yarn, leveraging the capability of Kerberos. So what are Spark features which really makes it unique or in-demand processing framework? When we talk about Spark features, one of the key features is fast processing. So Spark contains resilient distributed datasets. So RDDs are the building blocks for Spark, and we'll learn more about RDDs later. So Spark contains RDDs, which saves huge time taken in reading and writing operations. So it can be 100 times, or you can say 10 to 100 times faster than Hadoop. When we say in-memory computing, here I would like to make a note that there is a difference between caching and in-memory computing. Think about it. Caching is mainly to support read-ahead mechanism where you have your data preloaded so that it can benefit further queries. However, when we say in-memory computing, we are talking about lazy valuation. We are talking about data being loaded into memory only and only when a specific kind of action is invoked. So data is stored in RAM. So here we can say RAM is not only used for processing, but it can also be used for storage. And we can again decide whether we would want that RAM to be used for persistence or just for computing. So it can access the data quickly and accelerate the speed of analytics. Now, Spark is quite flexible. It supports multiple languages, as I already mentioned, and it allows the developers to write applications in Java, Scala, R, or Python. It's quite fault tolerance. So Spark contains these RDDs, or you could say execution logic, or you could say temporary data sets, which initially do not have any data loaded, and the data will be loaded into RDDs only when execution is happening. So these can be fault tolerant as these RDDs are distributed across multiple nodes. So failure of one worker node in the cluster will really not affect the RDDs because that portion can be recomputed. So it ensures loss of data. It ensures that there is no data loss, and it is absolutely fault tolerant. It is for better analytics. So Spark has rich set of SQL queries, machine learning algorithms, complex analytics, all of this supported by various Spark components, which we will learn in coming slides. With all these functionalities, analytics can be performed better in terms of Spark. So these are some of the key features of Spark. However, there are many more features which are related to different components of Spark, and we will learn about them. So what are these components of Spark which I'm talking about? Spark Core. So this is the core component, which basically has RDDs, which has a core engine which takes care of your processing. Now you also have Spark SQL. So people who would be interested in working on structured data or data which can be structurized would want to prefer using Spark SQL. And Spark SQL internally has components or features like data frames and data sets which can be used to process your structured data in a much faster way. You have Spark streaming. Now that's again an important component of Spark, which allows you to create your Spark streaming applications, which not only works on data which is being streamed in or data which is constantly getting generated, but you could also transform the data. You could analyze or process the data as it comes in smaller chunks. You have Spark's MLlib. Now this is basically a set of libraries which allows developers or data scientists to build their machine learning algorithms so that they can do predictive analytics or prescriptive, descriptive, preemptive analytics, or they could build their recommendation systems or bigger, smarter machine learning algorithms using these libraries. And then you have graphics. So think about organizations like LinkedIn or say Twitter, where you have data which naturally has a network kind of flow. So data which could be represented in the form of graphs. Now here when I talk about graphs, I'm not talking about pie charts or bar charts, but I'm talking about network related data. That is data which can be networked together, which can have some kind of relationship. Think about Facebook, think about LinkedIn, where you have one person connected to other person or one company connected to other company. So if we have our data which can be represented in the form of network graphs, then Spark has a component called GraphX, which allows you to do graph-based processing. So these are some of the components of Apache Spark: Spark Core, Spark SQL, Spark Streaming, Spark MLlib, and GraphX. So to learn more about components of Spark, let's learn here about Spark Core. Now this is the base engine, and this is used for large-scale parallel and distributed data processing. So when you work with Spark, at least and the minimum you would work with is Spark Core, which has RDDs as the building blocks of your Spark. So it is responsible for your memory management, your fault recovery, scheduling, distributing, and monitoring jobs on a cluster, and interacting with storage systems. So here I would like to make a key point that Spark by itself does not have its own storage. It relies on storage. Now that storage could be your HDFS, that is Hadoop's distributed file system. It could be a database like NoSQL database such as HBase, or it could be any other database, say RDBMS, from where you could connect your Spark and then fetch the data, extract the data, process it, analyze it. So let's learn a little bit about your RDDs, resilient distributed datasets. Now Spark Core, which is the base engine or the core engine, is embedded with the building blocks of Spark, which is nothing but your resilient distributed dataset. So as the name says, it is resilient. So it is existing for a shorter period of time, distributed. So it is distributed across nodes. And it is a data set where the data will be loaded or where the data will be existing for processing. So it is immutable, fault tolerant, distributed collection of objects. So that's what your RDD is. And there are mainly two operations which can be performed on an RDD. Now to take an example of this, say I want to process a particular file. Now here I could write a simple code in Scala, and that would basically mean something like this. So if I say val, which is to declare a variable, I would say val x, and then I could use what we call as Spark context, which is basically the most important entry point of your application. So then I could use a method of Spark context, for example, that is text file, and then I could point it to a particular file. So this is just a method of your Spark context, and Spark context is the entry point of your application. Now here I could just give a path in this method. So what does this step do? It does not do any evaluation. So when I say val x, I'm creating an immutable variable. and to that variable I'm assigning a file. Now what this step does is it actually creates a RDD, resilient distributed data set. So we can imagine this as a simple execution logic, a empty data set which is created in memory of your node. So if I would say I have multiple nodes in which my data is split and stored, imagining that your Spark is working with Hadoop. So I have Hadoop which is using say 2 nodes, and this is my distributed file system HDFS, which basically means my file is written to HDFS, and it also means that the file related blocks are stored in the underlying disk of these machines. So when I say val x equals sc.text file, that is using a method of Spark context. Now there are various other methods like whole text files, parallelize, and so on. This step will create an RDD. So you can imagine this as a logical data set which is created in memory across these nodes, because these nodes have the data. However, no data is loaded here. So this is the first RDD, and I can say first step in what we call as a DAG. A DAG which will have series of steps which will get executed at later stage. Now later I could do further processing on this. I could say val y, and then I could do something on x. So I could say x dot map, and I would want to apply a function to every record or every element in this file, and I could give a logic here, x.map. Now this second step is again creating an RDD, a resilient distributed data set. You can say second step in my DAG, okay, and here you have a external RDD, one more RDD created which depends on the first RDD. So my first RDD becomes the base RDD or parent RDD, and the resultant RDD becomes the child RDD. Then we can go further and we could say val z, and I would say, okay, now I would want to do some filter on y. So this filter which I am doing here, and then I could give a logic. Might be I'm searching for a word, I'm searching for some pattern. So I could say val z equals y.filter, which again creates one more RDD, a resilient distributed data set in memory. And a, you can say this is nothing but one more step in the DAG. So this is my DAG, which is a series of steps which will be executed. Now here, when does the execution happen? When will the data get loaded into these RDDs? So all of this, that is using a method, using a transformation like map, using a transformation like filter or flat map or anything else, these are your transformations. So the operations such as map, filter, join, union, and many others will only create RDDs, which basically means it is only creating execution logic. No data is evaluated, no operation is happening right now. Only and only when you invoke an action, that is, might be you want to print some result, might be you want to take some elements and see that, might be you want to do a count. So those are actions which will actually trigger the execution of this DAG right from the beginning. So if I here say z dot count, where I would want to just count the number of words which I'm filtering, this is an action which is invoked, and this will trigger the execution of DAG right from the beginning. So this is what happens in a Spark. Now if I do a z.count again, it will start the whole execution of DAG again right from the beginning. So my z.count, second time an action is invoked, again the data will be loaded in the first RDD, then you will have map, then you will have filter, and finally you will have result. So this is the core concept of your RDDs, and this is how RDD works. So mainly in Spark, there are two kinds of operations. One is your transformations and one is your actions. Transformations or using a method of Spark context will always and always create an RDD, or you could say a step in the DAG. Actions are something which will invoke the execution, from the first RDD till the last RDD where you can get your result. So this is how your RDDs work. Now, when we talk about components of Spark, let's learn a little bit about Spark SQL. So Spark SQL is a component a processing framework which is used for structured and semi-structured data processing. So usually people might have their structured data stored in RDBMS or in files where data is structured with particular delimiters and has a pattern. And if one wants to process this structured data, if one wants to use Spark to do in-memory processing and work on this structured data, they would prefer to use Spark SQL. So you can work on different data formats, say CSV, JSON. You can even work on smarter formats like Avro, Parquet, even your binary files or sequence files. You could have your data coming in from an RDBMS, which can then be extracted using a JDBC connection. So at the bottom level, when you talk about Spark SQL, it has a data source API, which basically allows you to get the data in whichever format it is. Now, Spark SQL has something called as data frame API. So what are data frames? Data frames, in short, you can visualize or imagine as rows and columns, or if your data can be represented in the form of rows and columns with some column headings. So data frame API allows you to create data frames. So like my previous example, when you work on a file, when you want to process it, you would convert that into an RDD using a method of Spark context or by doing some transformations. So in the similar way, when you use data frames or when you want to use Spark SQL, you would use Spark's context, which is SQL context or Hive context or Spark, which allows you to work with data frames. So like in my earlier example, we were saying val x equals sc.text file. Now in case of data frames, instead of sc, you would be using, say, Spark dot something. So Spark context is available for your data frames API to be used. In older versions like Spark 1.6 and so on, we were using Hive context or SQL context. So if you were working with Spark 1.6, you would be saying val x equals SQL context dot. Here we would be using Spark dot. So data frame API basically allows you to create data frames out of your structured data, which also lets Spark know that data is already in a particular structure. It follows a format, and based on that, your Spark's backend DAG scheduler, right? So when I say about DAG, I talk about your sequence of steps. So Spark is already aware of what are the different steps involved in your application. So your data frame API basically allows you to create data frames out of your data. And data frames, when I say, I'm talking about rows and columns with some headings. And then you have your data frame DSL language, or you can use Spark SQL or Hive query language. Any of these options can be used to work with your data frames. So to learn more about data frames, follow in the next sessions. When you talk about Spark streaming, now this is very interesting for organizations who would want to work on streaming data. Imagine a store like Macy's, where they would want to have machine learning algorithms. Now, what would these machine learning algorithms do? Suppose you have a lot of customers walking in the store and they are searching for particular product or particular item. So there could be cameras placed in the store, and this is being already done. There are cameras placed in the store which will keep monitoring in which corner of the store there are more customers. Now, once camera captures this information can be streamed in to be processed by algorithms, and those algorithms will see which product or which series of product customers might be interested in. And if this algorithm in real time can process based on the number of customers, based on the available product in the store, it can come up with a attractive alternative price, so that which the price can be displayed on the screen and probably customers would buy the product. Now this is a real-time processing where the data comes in, algorithms work on it, do some computation and give out some result, and which can then result in customers buying a particular product. So the whole essence of this machine learning and real-time processing will really hold good if and when customers are in the store. Or this could relate to even an online shopping portal where There might be machine learning algorithms which might be doing real-time processing based on the clicks which customer is doing. Based on the clicks, based on customer history, based on customer behavior, algorithms can come up with recommendation of products or better altered price so that the sale happens. Now, in this case, we would be seeing the essence of real-time processing only in a fixed or in a particular duration of time. And this also means that you should have something which can process the data as it comes in. So Spark Streaming is a lightweight API that allows developers to perform batch processing and also real-time streaming and processing of data. So it provides secure, reliable, fast processing of live data streams. So what happens here in Spark Streaming in brief? So you have an input data stream. Now that data stream could be a file which is constantly getting appended. It could be some kind of metrics. It could be some kind of events based on the clicks which customers are doing or based on the products which they are choosing in a store. This input data stream is then pushed in through a Spark Streaming application. Now, Spark Streaming application will break this content into smaller streams, what we call as discretized streams or batches of smaller data on which processing can happen in frames. So you could say process my file every 5 seconds for the latest data which has come in. Now there are also some Windows based options. Like when I say Windows, I mean a window of past 3 events. Window of past 3 events, each event being of 5 seconds. So your batches of smaller data is processed by Spark engine, and this processed data can then be stored or can be used for further processing. So that's what Spark Streaming does. When you talk about MLlib, it's a low-level machine learning library that is simple to use, scalable, and compatible with various programming languages. Now, Hadoop also has some libraries like you have Apache Mahout, which can be used for machine learning algorithms. However, in terms of Spark, we are talking about machine learning algorithms which can be built using MLlib's libraries, and then Spark can be used for processing. So MLlib eases the deployment and development of scalable machine learning algorithms. I mean, think about your clustering techniques. So think about your classification, where you would want to classify the data, where you would want to do supervised or unsupervised learning. Think about collaborative filtering and many other data science related techniques or techniques which are required to build your recommendation engines or machine learning algorithms can be built using Spark's MLlib. GraphX is Spark's own graph computation engine. So this is mainly if you are interested in doing a graph-based processing. Think about Facebook, think about LinkedIn, where you can have your data which can be stored, and that data has some kind of network connections, or you could say it is well networked. I could say X is connected to Y is connected to Z is connected to A. So X, Y, Z, A, all of these are, in terms of graph terminologies, we call as vertices or vertex, which are basically being connected. And the connection between these are called edges. So I could say A is friend to B. So A and B are vertices, and friend, a relation between them, is the edge. Now, if I have my data which can be represented in the form of graphs, if I would want to do a processing in such way, this could be not only for social media, it could be for your network devices, it could be a cloud platform, it could be about different applications which are connected in a particular environment. So if you have data which can be represented in the form of graph, then GraphX can be used to do ETL, that is extraction, transformation, load, to do your data analysis and also do interactive graph computation. So GraphX is quite powerful. Now, when you talk about Spark, your Spark can work with your different clustering technologies. So it can work with Apache Mesos. That's how Spark came in, where it was initially to prove the credibility of Apache Mesos. Spark can work with Yarn, which is usually you will see in different working environments. Spark can also work as standalone. That means without Hadoop, Spark can have its own setup with master and worker processes. So usually, or you can say technically, Spark uses a master-slave architecture. Now that consists of a driver program that can run on a master node. It can also run on a client node. It depends on how you have configured or what your application is. And then you have multiple executors which can run on worker nodes. So your master node has a driver program, and this driver program internally has the Spark context. So your Spark, every Spark application will have a driver program, and that driver program has a inbuilt or internally used Spark context, which is basically your entry point of application for any Spark functionality. So your driver or your driver program interacts with your cluster manager. Now, when I say interacts with cluster manager, so you have your Spark context, which is the entry point that takes your application request to the cluster manager. Now, as I said, your cluster manager could be, say, Apache Mesos, it could be Yarn, it could be Spark standalone master itself. So your cluster manager in terms of Yarn is your resource manager. So your Spark application internally runs as series or set of tasks and processes. Your driver program, wherever that is run, will have a Spark context, and Spark context will take care of your application execution. How does that do it? Spark context will talk to cluster manager. So your cluster manager could be Yarn, and in terms of when I say cluster manager for Yarn would be resource manager. So at high level, we can say a job is split into multiple tasks, and those tasks will be distributed over the slave nodes or worker nodes. So whenever you do some kind of transformation or you use a method of Spark context, an RDD is created, and this RDD is distributed across multiple nodes. As I explained earlier, worker nodes are the slaves that run different tasks. So this is how a Spark architecture looks like. Now we can learn more about Spark architecture and its interaction with Yarn. So usually what happens when your Spark context interacts with the cluster manager. So in terms of Yarn, I could say resource manager. Now we already know about Yarn. So you would have, say, node managers running on multiple machines, and each machine has some RAM and CPU cores allocated for your node manager. On the same machine, you have the data nodes running, which obviously are there to have the Hadoop related data. So whenever an application wants to process the data, your application via Spark context contacts the cluster managers, that is resource manager. Now what does resource manager do? Resource manager makes a request. So resource manager makes requests to the node manager of the machines wherever the relevant data resides, asking for containers. So your resource manager is negotiating or asking for containers from node manager, saying, hey, can I have a container of 1 GB RAM and 1 CPU core? Can I have a container of 1 GB RAM and 1 CPU core? And your node manager, based on the kind of processing it is doing, will approve or deny it. So node manager would say, fine, I can give you the container. And once this container is allocated or approved by node manager, resource manager will basically start an extra piece of code called app master. So app master is responsible for execution of your applications, whether those are Spark applications or MapReduce. So your application master, which is a piece of code, will run in one of the containers. That is, it will use the RAM and CPU core, and then it will use the other containers which were allocated by node manager to run the tasks. So it is within this container which can take care of execution. So what is a container? A combination of RAM and CPU core. So it is within this container, we will have a executor process which would run, and this executor process is taking care of your application related tasks. So that's how overall Spark works in integration with Yarn. Now let's learn about this Spark cluster managers. As I said, Spark can work in a standalone mode, so that is without Hadoop. So by default, applications submitted to Spark standalone mode cluster will run in FIFO order, and each application will try to use all the available nodes. So you could have a Spark standalone cluster, which basically means you could have multiple nodes. On one of the nodes, you would have the master process running, and on the other nodes, you would have the Spark worker processes running. So here we would not have any distributed file system because Spark is standalone and it will rely on an external storage to get the data, or probably the file system of the nodes where the data is stored, and processing will happen across the nodes where your worker processes are running. You could have Spark working with Apache Mesos. Now, as I said, Apache Mesos is an open source project to manage your computer clusters and can also run Hadoop applications. Apache Mesos was introduced earlier, and Spark came in and has existence to prove the credibility of Apache Mesos. You can have Spark working with Hadoop's Yarn. This is something which widely you will see in different working environments. So Yarn, which takes care of your processing and can take care of different processing frameworks, also supports Spark. You could have Kubernetes. Now that is something which is making a lot of news in today's world. It is an open source system for automating deployment, scaling, and management of containerized applications. So where you could have multiple Docker-based images which can be connecting to each other. So Spark also works with Kubernetes. Now let's look at some applications of Spark. So JP Morgan Chase and company uses Spark to detect fraudulent transactions, analyze the business spends of an individual to suggest offers, and identify patterns to decide how much to invest and where to invest. So this is one of the examples of banking. A lot of banking environments are using Spark due to its real-time processing capabilities and in-memory faster processing, where they could be working on fraud detection or credit analysis or pattern identification and many other use cases. Alibaba Group that uses also Spark to analyze large data sets of data such as real-time transaction details. Now that might be based online or in the stores. Looking at the browsing history in the form of Spark jobs, and then provides recommendations to its users. So Alibaba Group is using Spark in its e-commerce domain. You have IQVIA. Now this is a leading healthcare company that uses Spark to analyze patients' data, identify possible health issues, and diagnose it based on their medical history. So there is a lot of work happening in healthcare industry where real-time processing is finding a lot of importance, and real-time and faster processing is what is required. So healthcare industry and IQVIA is also using Spark. You have Netflix, which is known, and you have Riot Games. So entertainment and gaming companies like Netflix and Riot Games use Apache Spark to showcase relevant advertisements to their users based on the videos that they have watched, shared, or liked. So these are few domains which find use cases of Spark, that is banking, e-commerce, healthcare, entertainment, and then there are many more which are using Spark in their day-to-day activities for real-time, in-memory, faster processing. Now, let's discuss about the Spark's use case, and let's talk about Conviva, which is world's leading video streaming companies. So video streaming is a challenge. Now, if you talk about YouTube, which has data, you could always read about it. So YouTube has data which is worth watching 10 years. So there is huge amount of data where people are uploading their videos or companies are doing advertisements, and this videos are streamed in or can be watched by users. So video streaming is a challenge, and especially with increasing demand for high quality streaming experiences. Conviva collects data about video streaming quality to give their customers visibility into the end user experience they are delivering. Now, how do they do it? Apache Spark again. Using Apache Spark, Conviva delivers a better quality of service to its customers by removing the screen buffering and learning in detail about network conditions in real time. This information is then stored in the video player to manage live video traffic coming in from 4 billion video feeds every month to ensure maximum retention. Now, using Apache Spark, Conviva has created an auto diagnostics alert. It automatically detects anomalies along the video streaming pipeline and diagnoses the root cause of the issue. Now, this really makes it one of the leading video streaming companies based on auto diagnostic alerts. It reduces waiting time before the video starts. it avoids buffering and recovers the video from a technical error. And the whole goal is to maximize the viewer engagement. So this is Spark's use case, where Conviva is using Spark in different ways to stay ahead in video streaming related deliveries. So let's have a quick demo on setting up Spark on Windows and trying out the Spark's interactive way of working. For this, first thing is you will have to download Spark. Now you can just go to Google and type Spark download. And once you click on this link, it shows you a Spark release, a package type which says pre-built. So we will have to get a pre-built Apache Hadoop related Spark. So here I will choose say Spark 2.4.3 and I will choose pre-built for Apache 2.6, and then I can just click and download on this Spark 2.4.3 bin Hadoop 2.6 tar file. Once you click on this link, takes you to the mirror site, and you can just click on this link and download Spark 2.4.3. Once this is done, which I have already downloaded, here I can go to my downloads and it shows that I have a tar file. Now we will have to untar it or unzip it. So I can click on this link and I already have WinZip, which allows me to unzip Spark 2.4.3. I can choose a location. So I can say unzip, click on unzip, choose local, and then I can choose one of my folders. So I have already unzipped it here. And that's how my Spark 2.4.4 directory exists here, 2.4.3, I'm sorry. Now let's go and look into this directory and what it contains. So I can click on C drive and then Spark 2.4.3, and this has the folders which are required for us to use Spark. If you look in bin, we have different applications and commands which we can use. And if you also see, I would have added one of the utilities here. Either we can have the Win utils, because Spark will need Hadoop and we are planning to use Spark on Windows. So what we need is this. So I have in my desktop a Hadoop directory which has a bin folder, and here I have downloaded a Win utils executable file, which you can always search on internet, and you can say download Win utils .exe for Spark 64-bit, and then you can find the link from where you can download this. For example, we can click on this and here we can search for WinUtils. So here we have the link. I can open this link in a different tab, and this basically shows me WinUtils for Hadoop 2.7.1. Similarly, you can search for Hadoop 2.6 and you can download. However, 2.7 will also work fine. Now I have downloaded winutils.exe, and that's in this Hadoop folder. Within bin, I have this. So we need two things here. One is Spark, which is untarred and in a particular location, and then your Hadoop, which has bin, and this has WinUtils. Now, once you have these things, you can set your environment variables by just typing envir, go to your edit system environment variables, click on environment variables, and here if you see, I have added two variables. So you can just click on new, and then you can give your variable name as Hadoop_home, and then you can give the path where you have your Hadoop directory that contains bin and that contains winutil.exe. I also have added Spark home, which points to my Spark directory. Now, once you have this, you are ready to use your Spark on Windows in local mode. Once this is done, I can open up my command prompt, and here I need to go to my Spark directory. I can just say cd spark 2.4.3, and then I can do a dir/p, which shows me the folders where we have bin. So to execute Spark, we can look into what our bin has, and it has different programs, such as you have Spark Shell to work with Scala and in an interactive way of working with Spark. You can also use PySpark, which allows you to use Python to work with Spark. And you also have Spark Submit if you have packaged your application in a jar file to submit it on a cluster. So in this case, we would be using Spark in a local mode. So let's use Spark Shell and test it. So I can just say Spark shell in this way to start my Spark in an interactive way. Now, based on the path which you have set for your winutils.exe and Spark shell, you should be able to use Spark. So it says, welcome to Spark version 2.4.3. It also shows that Spark context, which is the entry point of your application, is available as SC, wherein it is connecting to master as local and it has an application ID. It also shows you a Spark UI, which you can look at, and it says Spark session is available as Spark. So if you're interested in working with Spark core, that is with RDDs, we would be using Spark context. And if you're interested in working with Spark SQL, that is data frames and data sets, then we can be using Spark session. So let's try it out. So we can declare a variable that is an immutable variable. And now I will use Spark context with a method of Spark context. So I could just do a tab to see what are the available options within your Spark context. And here we can use one of them to read a file. So I will use sc.text file, and then I need to point to a file. So I already know that in my Spark directory, I have a file called readme.rd, and this is the method of Spark context. If I enter, it will create a RDD. Now, as I've explained about RDDs, these are resilient distributed datasets. There is no evaluation happening right now. So even if this file does not exist, I would still have an RDD created. Now I can go further and do some more transformations on this. So I could say val y, and then I could say take x. I would like to do a map transformation on it, and I would use to uppercase. Now this is an inbuilt function where I would want to convert the content of this file into uppercase. When I hit on enter, it again creates an RDD, and this RDD is basically a child RDD of the parent RDD created by text file. Remember, here we don't have any evaluation happening or any execution happening. It is just transformations which will lead to creation of further RDDs. Now we can invoke an action to see the result, and whenever you invoke an action, it will trigger the execution of your DAG starting from your first RDD till the last transformation you did before invoking an action. So I could just say count to see how many lines it has, and once I do this, it says input path does not exist. It is not able to find a file in this location. So this clearly explains that there was no evaluation happening when we did this, when we tried to read a file, and neither when we did a map transformation. Only and only when we invoked an action, it tried to search for file in this location. So let's quit this and check if the file exists. To quit, you can just do a Control D, or you could do a :quit. Now here, if you see some messages like this which says unable to delete temporary file, so that's a known issue. We can fix that, but my Spark is working fine. Now let's go and check if the file exists. So I will go in here, and then I will look in my Spark directory to see if the file exists. So this is the file readme.md. However, I had done readme.rd. So let's do it again, and let's test if our Spark shell works fine. So we can go into the Spark directory by just doing this. And then either I could be going into bin directory and then start Spark shell, or some people prefer to do it this way, wherein you can say bin Spark shell, and that should start your Spark shell, but there was an error in the slash. So let's do it this way, and this will start your Spark shell, an interactive way of working with your Spark and using Spark context or Spark. Now once we have done this, I can again say val x, and I can say sc, which is Spark context, which is already initialized when you start your Spark shell. I can say text file, and I would want to read a file which is readme.md. Now we know that this file exists. However, the checking of the file existing or not, that means an evaluation, does not happen when you do a transformation or when you use a method of Spark context. It just creates an RDD. Click on this, and this has created an RDD of string. Now we can do further transformation on X by saying map, and then I can say I would want to convert the content into uppercase, and that's also done. Now finally, let's invoke an action which will trigger the execution of my tag which contains these RDDs. So I could just say y, and I could say take 10, and I could say for each print ln, and this should be able to invoke an action, and it shows me the result from the file which is converted into uppercase. Remember, if I do a y.count, which is another action, it will trigger the execution of DAG right from the beginning where the first RTD was created. The transformation will be done, and then it will show me the count of lines which exist as a result of this. So we can do this, and this says me that there are 105 lines. This is a simple example of using Spark shell and using Spark in an interactive way on your Windows machine. Now to quit, we can always do a :quit, or we could do a Control D, and that basically takes you out of your Spark shell. Similarly, we can work on PySpark by just saying ./bin/PySpark, and that's Python's way of working with Spark, which brings your Python shell. It starts the Spark context, which is available as SC. And if you are interested in working on data frames or data sets using Spark SQL, then we would be using Spark. Now here, I can just declare a variable x, and I can just do sc.text file like what we did using Scala. We can be referring to the same file, readme.md, and this has created an RDD. You can just type in x, and that shows the RDD which was created. You can then further do some transformation on it using x.map, and then I could say I would want to convert this to uppercase. Now in case of Python, you would normally use lambda if you would want to do any kind of transformation. So I would say lambda x, and then I would want to convert this to uppercase. So here we can check if my RDD was correctly created, and as I was saying, we can then do some transformation on it. So I can say again y equals, and then I would want to do some transformation on x. I would say x.map. So in case of Python, as I explained, whenever we want to use an anonymous function or we want to do some transformation, then we can pass in the function to the transformation. So here I can say lambda, and then I can just say line, or I could say x or a, whatever that is, and I could say line. I would use an inbuilt function that is upper, which should convert the content of x to uppercase. Now remember, we are just doing some transformations here. So if I click on y again and if I enter y, it will show me that that has created an RDD. To see the content, I can just say y.collect, and that should show me the content of first few lines, which is converted in uppercase. So this clearly shows that we can even use Python to work with Spark by using PySpark. Now to quit this, we can just say quit, and that should take you out of your PySpark shell. So this is how you work on Spark shell or PySpark on your Windows machine. So this has a local Spark setup, or basically Spark running in a local mode, and you could be using the interactive way of working with Spark. Now if we have packaged our application in a jar file, then I could be using Spark submit to submit my application. How do we do that? For this, we can basically bring up one of our IDEs. So in my case, I'm using Eclipse, and I can get into my Eclipse. Now there are two options here. One, we can be writing code in your IDE, that is Eclipse. We can be compiling the code based on the Spark related jars, and then we can run our application from IDE, which would interact with your Spark. That's one way. The second way is we can use packaging tools like SBT to package our application as jar, and then push the jar to your local Spark or a Hadoop based Spark, and then run it using Spark Submit. Now this is a simple sample application for which I have set up certain things here. The first thing is, when you have downloaded Eclipse, for all the people who are new, they might have to add the Scala plugin. Now, if you see here in my Eclipse, it shows up Java perspective and it shows Scala perspective. Now, how did I get this? You can click on help and you can say install new software. And here you can say add, you can say Scala IDE, and then you will have to give a link from where you can get the Scala IDE. How do I get that? So I can go to my browser and I can say scalaide.org. And once you go to this link, just scroll down, click on stable, and that shows you different releases for your different IDEs. Now for Eclipse, although this shows for Oxygen and I have Eclipse Neon, but that works fine. You can just copy this link, and here, once you have copied the link, give the location here, and you can say OK. Now once you do that, it shows you different options from where you can choose Scala IDE for Eclipse. Now in my case, it is already installed, so these options don't show up. However, if you do not have this option, for example, let's choose something else. Say I will say Scala search, and once I do this, next gets activated. So Scala IDE is already installed in my case, so I can click on next, and this should basically get Scala search plugin also, which can be added to my Eclipse. Now once this is done, you will be prompted to restart your Eclipse, and then you should have your Scala perspective. So for now, I'll just cancel this because I already have my Scala IDE.eclipse. So this is done. I'll just do a cancel here. Now once you have your Scala IDE or Scala plugin added to your IDE, you can always click on this icon here, and here you can just double click on Scala. That will open up Scala perspective. So that's the first thing. Then you can always click on File, New, and create a Scala project. For example, I could say My Test Apps, and then I can just say finish. So it has added a project. Now what we need to do is we need to make sure that our setup is fine. So first thing I would suggest is click on this, go to your build path, and here click on configure build path. So where it says Scala compiler, it would be good to choose for your project settings, instead of 2.12, go for 2.11. So sometimes you might have problems with Scala 2.12, which might not be able to compile for your Scala 2.11. So use latest 2.11 bundle, and then you can say apply. It says compiler settings have changed. A full rebuild is required for changes to take effect. Shall all projects be clean now? We can say OK, and we can say OK. So this will build your workspace to use Scala 2.11 bundle. Now once that is done, second thing what we need is we would want to write our code, and we would want our code to compile. For that, as I said, if we want to write our code using an IDE and then run it from our IDE rather than using a build tool like Maven or SVT, I can just add the Spark related jars to my build path. So I can right click here, I can say build path, and I can click on configure build path, and here where it says libraries, I can say add external jars. Now this needs my Spark related jars. Now where do I find it? So remember, we have downloaded Spark, so you can even find it there. So you can click on wherever your Spark is, and then you can click for jars, which shows you all Spark related jars. You can just do a Control A and just add it to your build path, say apply, and then just say OK. So once this is done, you have already added the Spark related jars, which might be good enough for you to write an application. Once this is done, we need to basically go ahead and write our code. Now how do I do that? I can just click on source and I can say new, and then I can say package, and here you can say main.scala. Click on finish, and that has created main.scala. So that would be source/main/scala in the folders. We can always check that. So I can go to C drive, I can look in users, Win10, and then look in my workspace for my project. And if you see in source, we have main and we have Scala. Now this is where we will be writing our code. So for this, then I can just right click and I can say new, and I can just create an object and I can give it a name. So we can say test app and then we can say finish. So in case of Scala and Spark, we need to create an object and then we need to define main class here. Once that is done, we also need to import some packages and we need to initialize the Spark context. Now for that, you can take an example here. So I have already written the code and I can look in source, main Scala, and I have created an app called firstapp.scala. Now here we have the package name. We are importing some packages which are required for us to initialize Spark context and Spark configuration. So it is Spark context, Spark conf, and here is my object. And for a particular project, at least one of your object or one of your application needs to be the main. So we define the main here by saying def main args and array of string. Then we need to basically define our Spark context. So I'm creating a configuration object here and then I say new Spark conf. I'm setting my application name to Hello Spark. And then this is very important. If you intend to run your Spark application either using Spark Submit or from your IDE, you need to specify your master as local. Now that could be given with one thread or multiple threads. So this is my configuration and then I initialize my Spark context pointing to my configuration. So this is the most important part here. Now, if you see, this is something which I showed you in the command line. So I'm doing a val x and I'm pointing it to a file in my project directory, which is abc1.txt. So this is just to make sure that you are giving a Windows path and you're giving the right escape characters. Now, if you intend to run this application on a Hadoop based cluster, then you will have to give the path of the file accordingly, which we can see later. So here I have val x, I'm pointing it to a file which I have created here. And this just contains 3 lines. This is my sample file, which I want to test. This is a new file. Now here I've created a variable called x. Further, I would say val y and I would use Spark context method text file like what we did in an interactive way, and I'm pointing it to x. I'm also using some extra features like caching so that I can cache the RDD which gets created. Further, I create a variable called counts and then I do a flat map transformation on y, where I would split the content based on space. I would do a map transformation where I would get every word from the file and map it with number 1. And finally, I do a reduce by key operation. Once this is done, I do a saves as text file. Now I could do a collect, I could do a take, I could do a count, and I could also do a save as text file where I would want my output to be saved in this location. Plus I'm using a Java utility to append a random number to my output directory. Finally, I do a Spark context stop. So this is my application. And if you see here, my application completely compiles because I've already added the relevant jar files in the build path. Now, once this application is done, we need to run this. But before doing that, we need to look into our run configurations. So you can click on run configurations. And here I'm giving my project name. I'm specifying my main class, which is first app. Then you can straight away go to environment. And here I have added 2 variables. One is spark underscore local underscore IP, which points to this machine's local host. And then I've said Hadoop underscore home because Spark, even when you're running locally, would want if Hadoop is existing. So we can just set Hadoop underscore home and I'm pointing it to my desktop Hadoop directory, which contains bin folder, and that bin folder contains a winutils.exe. Once this is done, we are fine, and then I can test my application by just clicking on run. Now this should trigger my application on my Windows machine using my IDE. I didn't have to package this as jar, and here my application is completed, which should have created one additional directory here. So I can click on this, I can right click, and I can try doing a refresh. And here you see a new output is created. We can look into this. It has a part file which shows my word count. So this is a simple example of setting up your IDE and running your applications from IDE on a local Spark. Now what you also see is a build file here. What is that for? So in case you would want to create a project and you would want to package the application as a jar file and then run it on the cluster using Spark Submit. Now in that case, we can avoid adding the jars to my build path. But what I would need is I would need build.sbt file within my project folder. Remember, if you intend to package your application as a jar and then run it on a cluster or on a local setup, you would not need the build related jars. However, the build related jars which are already here will not cause any harm. Let them be there. Now we have a build.sbt file also which is existing in my project folder. Now just for this run, I can in fact delete this target directory. It will be anyways recreated, and if you would want, we can also clean up these just to avoid the confusion. I will delete these. Now I just have my project folder and I have the libraries. I have abc1.txt and I have a build.sbt file. What does that contain? So this basically has a name. I'm giving a version which will be appended to my jar. I'm saying the Scala version which I'm using, which is 2.11.8, and I'm saying Spark version which is 2.2.0. You can replace these with the version which you intend to use. Other than that, we are pointing to the different Spark components and the relevant dependency related jars which your SBT can get for you. So I've given Spark Core, Spark SQL, MLlib, Spark Streaming, and Spark Hive, which will be then fetched from the repository. So this is my build.sbt file, which exists in my project folder. We have our code written. We have our build.sbt file, which is already existing in my project folder. My code is already fine. Now we need to use SBT to package my applications into jar, for which you will have to download SBT. So you can just say download SBT Windows, and that should take you to the installing SBT on Windows page. Now here you can just download the MSI installer and run through the installer, which will basically install SBT on your machine. Now I have already done that. So my build file is ready, my code is ready. All I need to do is now use SBT. So what I can do is from my command line, I can just say cd and I will go into users. I'll go into Win10 and I'll go into my workspace. Now here I can see for my projects and I can go into my Spark apps. Now once I'm in my project folder, we can double check that it has a build.sbt, which is fine. SBT is already installed on this machine. And I can just say SBT. If you would want to check, you can always do SBT version to check if you have SBT. And this command is also done once you install SBT for the first time. You can always do SBT version, and before displaying SBT's version, it will try to fix all your dependencies. It will try to get all the relevant dependencies. So this is just to check that SBT is installed on my machine. As I said, my code is already ready. I have a build.sbt file and I can just say SBT package, which then will refer to build.sbt, will look for your code in source main Scala, and then if everything is fine, it will package it as jar and it will create folders within your project folder. We can click on this. We can try doing a refresh to see. Now, if you see here, the project was again created. A target folder is created. Within Scala 2.11, I will have my jar created. So we can see that my SBT was fine. It has packaged the code and it has created a jar file as simple project 2.11-1, which can be used to run on the cluster or in a local mode. Let's check in Eclipse. I'll click on this and I'll just do a refresh, and I see my jar is already existing, which basically means then we can do a Spark submit. So this is where we see that I am already running a Spark submit command. Now this might show up some error messages, but we can see how we did this. So if you see here, once my packaging was done, I went into my Spark folder. I did a bin/Spark submit. I mentioned my jar file, and then I said my class main.scala.firstApp. So this is my app, and this is how I'm using Spark submit to submit an application which is running in local mode. So we can see further if it starts processing. So here it says created local directory, then it starts an executor on local host. It goes for execution, and then if we see further, we could also see it will add our jar to the class path, and then finally it should be doing the execution. Now, if there is any error message that might be related to your file not being deleted, or if there is any problem with executor, so we can basically come back and check here if there was any specific error. So the error was that it tries to delete a temp directory, but it does not have the permissions, so we have not done that. But as per my application, it should be creating a output in this folder as Spark out. So let's click on this and see. I'll do a refresh, right? And if you see, a new Spark output has been created. Previous sessions, we have seen how we can set up Spark on Windows or set up our Spark related IDE so that we can run our applications on Windows. Now here we have a quick demo on setting up Spark as a standalone cluster on Ubuntu machines, and then trying out Spark way of working, for which we need at least 2 machines. And here I have Ubuntu machines set up, UM1 and UM2, just to give insights on how my machines look. So if I look in my etc hosts, I have the IP address of multiple machines, so I can ping one machine to other machine by just doing a ping UM2, and that should work fine. Similarly, I have also set up SSH access for these machines. Both of the machines have HDU as the user, and I can just do a SSH UM2, and that logs me into the second machine without a password. Similarly, I can check the same thing from my second machine by doing a SSH UM1, and that works fine too. So we need 2 machines which can ping each other, firewall disabled, able to SSH each other, so that we can set up a standalone cluster of Spark. How do we do it? So first thing is we will have to download the Spark related tar file. Now I can just go to Google and I can type in Spark 2.2.1 download. Now that's what I'm interested in, and this takes you to Spark release 2.2.1. However, here it shows you the latest release is 2.4 and then 2.4.2. So what we can do is we can go to archives. So I can basically look at existing versions. Now here I can click on download, and this shows me a Spark release and also pre-built for Apache Hadoop. Now what we can also do is we can go to release archives for an older stable version. I click on this, and here I have Spark 2.2.1. Now I can click on this and we can either install something which is not already built, or we can download this one, which is Spark 2.2.1 bin Hadoop 2.6.tgz. So you click on this link and then save this file, which I have already done. And here, if you see in my machine, I have home HDU downloads, which has my different packages which I've downloaded. Also, if you notice, I have downloaded JDK8, so you can check on my machines. So apart from machines being able to ping each other and being able to do a SSH, we also need machines to have Java, which is already installed. Once this is done, now I have my Spark related package. So I go into user local directory, and then you can give a command here, that is sudo tar xvf home hdu downloads, and then give your Spark package. Now once you do this, this will untar the Spark directory and create a directory in my user local location. If you see here, this is the directory which is created, but you also see that there is a Spark link which is pointing to Spark. Now that is because if you would want to work on a newer version of Spark, you could just do the same thing for newer version and then make your link pointing to the newer version of Spark. How do you create a link? You can just say sudo ln -s, you can give your Spark directory, and then you can create a link. So I've already created a link, and my Spark path will then become this. Now what do we do with this? Once we have done this, once we have created a link, we can go into the bash file of my user. And if you carefully see here, I have given my Java path so that I can execute Java related commands. And I have also added my Spark related path here, which says user local Spark. So in case you would be changing your Spark version to a latest one, you will not have to change things in your bash file. Only thing you will have to do is unlink the existing Spark link and create a new link to your newer version. So this is done on this machine, and now I can basically be using Spark. Now before doing that, we can go into user local Spark, and this has different directories. So if you look in bin, these has the binaries programs like your PySpark, your Spark Shell, Spark SQL, and Spark Submit, which we will see how we can use here. If you look in sbin, it has other startup scripts to start your history server or to start your master or worker processes. If you look in conf, this has your config directories. Now here by default, you might see spark -default.conf.template. I have renamed that to .conf. Slaves template has been renamed to slaves. So let's look into this. So I can go into conf, and then I will look in spark default conf. Now here, based on our setup, now here we intend to set up a Spark standalone cluster that is without Hadoop, but I would want to have a Spark standalone distributed cluster. So I have uncommented this property which says spark.master, and I say Spark, and I also mentioned that my master will run on this machine, which is UM1. Spark event log .enabled is true because we would want to track the events. I have mentioned a directory, so this is a local directory in user local Spark, and we will have to create it. It talks about the default serializer. It talks about the driver memory, which was by default 5 GB. I have reduced it to 2 GB based on my machine configuration. You have Java options. And then if you intend to run a history server so that whenever your Spark applications complete, you will have your application stored in history server, I have given the log directory, which is user local Spark, and then application history, and this also needs to be created. We have Spark history provider for the class, which takes care of history server, and the update interval of looking for your applications. So this is what we have in our Spark default. And if you look in slaves, I have given the machines where I would want my worker processes to run. So that is UM1 and UM2. Now, once you have made your changes in your Spark default conf and slaves file, what you can simply do is SCP, assuming that whatever was done on this machine, that is untarring your Spark directory, creating a link, updating your bash RC, and renaming your config files, same steps need to be done on the second machine, and your second machine would also be prepared to be used for your Spark cluster. So once you have both the machines which can ping each other, which can SSH each other, both of the machines have Java, both of the machines have the same Spark version downloaded, and the basic setup done, I can just easily copy the Spark related config from here into my other machine, that is SDU UM2, and then I can give a path which is user local Spark conf, and in this way I don't need to edit my config files again, and similarly I can even copy the slaves file. This is all we need to basically have our Spark standalone cluster. Now, since we have updated our bash RC, we can give our Spark commands from anywhere. We have set up our config files, so I can just do a start -all.sh, and that based on my config files, based on the directories which are mentioned, it will start my master process and my worker process on both the machines. So here we have a Spark standalone cluster which has 2 workers and 1 master. Now we can always go to the browser interface and we can check for the Spark UI, which should be available by typing in http:// my master, and then the port is 8080. So this shows that I have a Spark master running. I have 2 worker processes. Right now there are no applications which are running, but my Spark UI is already available. When we start using Spark, either by Spark Shell or PySpark or even Spark Submit, we will see our applications getting populated here. Additionally, we can also start the start history server by just saying start history server.sh, and that will start my history server. Once this is done, we have a history server also running, and we can go back and then we can again pull out the history server user interface by giving in the port which is default 18080. So I have a Spark standalone cluster with 1 master, 2 workers, and also a history server which is running. Once we have this, we can try working with Spark, either with Spark Shell or PySpark, or if you have packaged your application as a jar using SBT or Maven, you could also use Spark Submit. Additionally, you could also use Spark SQL. So to work with Spark, I would just say Spark Shell on one of my machines. Both my machines which have worker processes running, we can start our Spark Shell on any of these machines. Remember, here our Spark will rely on the storage of these machines, that is the file system, because it does not have any Hadoop or distributed file system. We have started our Spark Shell, and that shows Spark Context, which is available as SC. Spark Session is available as Spark. So to work with Spark Core and RDDs, we would be using Spark Context, and if you intend to work with Spark SQL, that is data frames and data sets, you can be using Spark. Let's try a quick simple example. So I'll say val x sc.text file, and now I would want to point it to a file. So I will say the complete path. Remember, I'm giving the Spark command from my home directory. So I will have to say user local spark, and then I can point to a file which is existing here. And this is what I would want to use to do some processing. We are using the first step here, wherein we are using a method of Spark Context which will not relate in any evaluation, and it will just create an RDT. Now we are using the Scala's way, so let's create one more variable, and then we can do some transformation on it by saying to uppercase. I would just want to convert the content into uppercase, and this is again a transformation, so that will just create an RDT. Once this is done, we can invoke an action to basically see some results. So I could just simply do a collect, which is an action, and this action will trigger the execution of DAG, which starts from the farthest RDD. That is the first step where your file is loaded into RDD. Now once we do this, we should be able to see our result, and that basically is execution of DAG. So from the time we have used a text file, which is a method of Spark Context, to we did a transformation, and till we invoked an action becomes my one job. Now if I would do y.count, which is again a different action, this will trigger the execution of DAG right from the beginning. That is sc.text file, where the data will again be loaded in RDD. A map transformation will happen, and then you will have a count. Now we can always see this in the Spark UI by just going in here and just doing a refresh. So that will show me that there is an application which is running via Spark Shell. It has utilized 3 cores. It has utilized memory per executor 1 GB, and we can click on this application, which shows that it used both the workers, 1 core and 1 GB on this worker, and 2 cores and memory on this worker. I can click on application detail UI, wherein I can see what are the actions I invoked. We also see the number of tasks which are run, and that is because every RDD which is created by default is having 2 partitions. and for each partition you would have one task. Well, we can change the partitions and many more things can be done, but that you can learn in later sessions. Here we have two jobs, one ended with collect and one ended with count. Now I can click on collect and I can see the DAG visualization, which tells me we started with a text file, we did a map, and finally we did a collect. It shows that everything was done in stage 0. That is just one stage. I can click on count, and that again shows me the DAG visualization, which is a different stage, a different job ID, which started with text file, map, and then we did a count. If you would want to see more details, you can always use these tabs to look at different stages within your application. If you were doing some caching, looking at environment variables, and also to see how many executors were used, including the one for the driver, on which nodes these executor ran, how many cores, how many tasks were run, was there any shuffling involved, and so on. So this is how I have used Spark Shell. That is an interactive way of running my application. And since we have a Spark UI, we can always look at applications when they have run, and we can always drill down and know more details. Now, since my application is completed, I can do a refresh on history server, but that does not show anything because when we started a Spark Shell, it started an application and that application is still in running status. If you see here under running applications. So this is how we use Spark Shell on a standalone Spark cluster. Now we can just do a :quit and that takes me out of Spark Shell. Similarly, if I would want to work on PySpark, that is Python's way of working with Spark, I can just type in PySpark, which should bring my Python shell, and then I can continue working with Spark and again go back and look at my UI. While my PySpark comes up, I can go here. Since I quit my Spark shell, I can just do a refresh to see if my application is yet coming up in history server. It might take some time, and you can always go back and look at incomplete applications or wait till your application is populated in history server. Now, if I do a refresh here on Spark UI, it says this application was completed. It says finished. And then now we have started PySpark. So it has started a new application, PySpark shell, and that is in running status. We can come back here and now we have our Python's way. So I can do the same thing which I did in Scala using sc.text file. I will point it to a file which exists in user local spark readme.md. So that's the file which I'm interested in. Now this would have created an RDT which we can confirm by just typing in X. Now I can create a different variable and I can say I would want to do a transformation of map. Now in case of Python, when you use anonymous functions or when you want to apply some functions to your transformations, you use lambda functions. So we say lambda line, and then I would say what I want to do to the line. I will say I will use a inbuilt uppercase upper function which should convert my content into uppercase, but as of now this is a transformation, so it only creates an RTT. To see the result, I can do a y.collect and that should bring up my result. Now in case if it says the file does not exist, that is because there was a typo here, and we can repeat this step. So let's bring up here again X, and I can give the right name of the file. I can do a transformation, and finally I can see the result. So this is using PySpark on a standalone Spark cluster, which is working without Hadoop, which has 2 worker nodes and 1 master node. We can always come and do a refresh here to look at more details. So we have our application. We can click on this. Again, similarly, like we did for Scala application detail UI, I see my application ended at collect, it ran 2 tasks, and I can look at my DAG. So this is how we can use Spark Shell or PySpark.
Thank you, Ajay. Now we have Rahul who will tell us how to become a big data engineer.
Now let's find out who is a big data engineer. A big data engineer is a professional who develops, maintains, tests, and evaluates the company's big data infrastructure. In other words, develop big data solutions based on a company's requirements. They maintain these solutions. They test out these solutions as to the company's requirements. They integrate this solution with the various tools and systems of the organization. And finally, they evaluate how well the solution is working to fulfill the company's requirements. Next up, let's have a look at the responsibilities of a big data engineer. Now, they need to be able to design, implement, verify, and maintain software systems. Now, for the process of ingesting data as well as processing it, they need to be able to build highly scalable as well as robust systems. They need to be able to extract data from one database, transform it, as well as load it into another data store with the process of ETL, or the extract transform load process. And they need to research as well as propose new ways to acquire data, improve the overall data quality and the efficiency of the system. Now, to ensure that all the business requirements are met, they need to build a suitable data architecture. They need to be able to integrate several programming languages and tools together so that they can generate a structured solution. They need to build models that reduce the overall complexity and increase the efficiency of the whole system by mining data from various sources. And finally, they need to work well with other teams, ones that include data architects, data analysts, and data scientists. Next up, let's have a look at the skills required to become a big data engineer. The first step is to have programming knowledge. One of the most important skills required to become a big data engineer is that of experience with programming languages, especially hands-on experience. Now, the big data solutions that organizations would want you to create will not be possible without experience in programming languages. I can even tell you an easy way through which you can get experience with programming languages. Practice, practice, and more practice. Some of the most commonly used programming languages used for big data engineering are Python, Java, and C++. The second skill that you require is to have in-depth knowledge about DBMS and SQL. You need to know how data is maintained as well as managed in a database. You need to know how SQL can be used to transform as well as perform actions on a database, and by extension, know how to write SQL queries for any relational database management systems. Some of the commonly used database management systems for big data engineering: MySQL, Oracle Database, and the Microsoft SQL Server. The third skill that you require is to have experience working with ETL and warehousing tools. Now, you need to know how to construct as well as use a data warehouse so that you can perform the ETL operation, or the extract, transform, and load operations. Now, as a big data engineer, you'll be constantly tasked with extracting unstructured data from a number of different sources, transforming it into meaningful information, and loading it into other data storages, databases, or data warehouses. Now, what this is basically aggregating unstructured data from multiple sources, analyzing it so that you can take better business decisions. Some of the tools used for this purpose are Talent, IBM DataStage, Pentaho, and Informatica. Next up, we have the fourth skill that you require, which is knowledge about operating systems. Now, since most big data tools have unique demands, such as root access to operating system functionality as well as hardware, having a strong understanding of operating systems like Linux and Unix is absolutely mandatory. Some of the operating systems used by big data engineers are Unix, Linux, and Solaris. Now, the fifth skill that you require to have experience with Hadoop-based analytics. Since Hadoop is one of the most commonly used tools when it comes to big data engineering, it's understood that you need to have experience with Apache Hadoop-based technologies. Technologies like HDFS, Hadoop MapReduce, Apache HBase, Hive, and Pig. The sixth skill that you require is to have worked with real-time processing frameworks like Apache Spark. Now, as a big data engineer, you'll have to deal with vast volumes of data. So, for this data, you need an analytics engine like Spark, which can be used for large-scale real-time data processing. Now, Spark can process live streaming data from a number of different sources like Facebook, Instagram, Twitter, and so on. It can also perform interactive analysis and data integration. And now we're at our final skill requirement, which is to have experience with data mining and modeling. So, as a data engineer, you'll have to examine massive pre-existing data so that you can discover patterns as well as new information. With this, you'll create predictive models for your business so that you can make better informed decisions. Some of the tools used for this are R, RapidMiner, Weka, and Nime. Now let's talk about a big data engineer's salary as well as other roles they can look forward to. Now, the average salary of a big data engineer in the United States is approximately $90,000 per year. Now, this ranges from $66,000 all the way to $130,000 per annum. In India, the average salary is around 7 lakh rupees and ranges from 4 lakhs lakhs to 13 lakhs per annum. After you've become a big data engineer, some of the job roles that you can look forward to are that of a senior big data engineer, a business intelligence architect, and a data architect. Now let's talk about certifications that a big data engineer can opt for. First off, we have the Cloudera CCP data engineer. A Cloudera certified professional data engineer possesses the skills to develop reliable and scalable data pipelines that result in optimized datasets for a variety of workloads. It is one of the industry's most demanding performance-based certification. CCP evaluates and recognizes a candidate's mastery of the technical skills most sought after by employers. The time limit for this exam is 240 minutes and it costs $400. Next, we have the IBM Certified Data Architect Big Data Certification. An IBM Certified Big Data Architect understands the complexity of data and can design systems and models to handle different data variety, including structured, semi-structured, unstructured, volume, velocity, veracity, and so on. A big data architect is also able to effectively address information governance and security challenges associated with the system. This exam is 75 minutes long. And finally, we have the Google Cloud Certified Data Engineer. A Google Certified Data Engineer enables data-driven decision making by collecting, transforming, and publishing data. They should also be able to leverage, deploy, and continuously train pre-existing machine learning models. The length of the certification exam is 2 hours and its registration fee is $200. Now let's have a look at how Simplilearn can help you become a big data engineer. Simplilearn provides the Big Data Architect Master's Program. This includes a number of different courses like Big Data Hadoop and Spark Developer, Apache Spark and Scala, MongoDB Developer and Administrator, Big Data and Hadoop Administrator, and so much more. This course goes through 50 plus in-demand skills and tools, 12 plus real-life projects, and the possibility of an annual average salary of 19 to 26 lakh rupees per annum. It will also help you get noticed by the top hiring companies. This course will also go through some major tools like Kafka, Apache Spark, Flume, HBase, MongoDB, Hive, Pig, MapReduce, Java, Scala, and much more. Now why don't you head over to simplilearn.com and get started on your journey to get certified and get.
Thank you, Rahul. Now, we will have a look at the Hadoop interview questions and answers. Our instructor Ajay will guide us through it.
One single machine with huge amount of disks and huge amount of RAM, but then the time taken to read that data when all the data is stored in one machine would be very high, and that would be with least fault tolerance. If you talk about HDFS, your data is distributed. So HDFS stands for Hadoop Distributed File System. So here your data is distributed and maintained on multiple systems. So it is never one single machine. It is also supporting reliability. So whatever is stored in HDFS, say a file being stored, depending on its size, is split into blocks, and those blocks will be spread across multiple nodes. Not only that, every block which is stored on a node will have its replicas stored on other nodes. Replication factor depends, but this makes HDFS more reliable. In cases of your slave nodes or data nodes crashing, you will rarely have data loss because of auto replication feature. Now, time taken to read the data is comparatively more, as you might have situations where your data is distributed across the nodes, and even if you are doing a parallel read, your data read might take more time because it needs coordination from multiple machines. However, if you are working with huge data which is getting stored, it will still be beneficial in comparison to reading from a single machine. So you should always think about its reliability through auto replication feature, its fault tolerance because of your data getting stored across multiple machines, and its capability to scale. So when you talk about HDFS, we are talking about horizontal scalability or scaling out. When you talk about regular file system, you are talking about vertical scalability, which is scaling up. Now, let's look at some specific HDFS questions. What is this? Why is HDFS fault tolerant? Now, as I just explained in previous slides, your HDFS is fault tolerant as it replicates data on different data nodes. So you have a master node and you have multiple slave nodes or data nodes where actually the data is getting stored. Now, we also have a default block size of 128 MB. That's the minimum since Hadoop version 2. So any file which is up to 128 MB would be using one logical block. And if the file size is bigger than 128 MB, then it will be split into blocks, and those blocks will be stored across multiple machines. Now, since these blocks are stored across multiple machines, it makes it more fault tolerant, because even if your machines fail, you would still have a copy of your block existing on some other machine. Now, there are two aspects here. One, we talk about the first rule of replication, which basically means you will never have two identical blocks sitting on the same machine. And the second rule of replication is in terms of rack awareness. So if your machines are placed in racks, as we see in the right image, you will never have all the replicas placed on the same rack, even if they are on different machines. So it has to be fault tolerant, and it has to maintain redundancy. So at least one replica will be placed on some other node on some other rack. That's how HDFS is fault tolerant. Now, here let's understand the architecture of HDFS. Now, as I mentioned earlier, you would, in a Hadoop cluster, the main service is your HDFS. So for your HDFS service, you would have a name node, which is your master process running on one of the machines, and you would have data nodes, which are your slave machines getting stored across, or the processes running across multiple machines. Each one of these processes has an important role to play. When you talk about HDFS, whatever data is written to HDFS, that data is split into blocks depending on its size, and the blocks are randomly distributed across nodes. With auto replication feature, these blocks are also auto replicated across multiple machines, with the first condition that no two identical blocks will sit on the same machine. Now, as soon as the cluster comes up, your data nodes, which are part of the cluster and based on config files, would start sending their heartbeat to the name node. And this would be every 3 seconds. What does name node do with that? Name node will store this information in its RAM. So name node starts building a metadata in its RAM, and that metadata has information of what are the data nodes which are available in the beginning. Now, when a data writing activity starts and the blocks are distributed across data nodes every 10 seconds will also send a block report to name node. So name node is again adding up this information in its RAM, or the metadata in RAM, which earlier had only data node information. Now name node will also have information about what are the files. The files are split in which blocks, the blocks are stored on which machines, and what are the file permissions. Now, while name node is maintaining this metadata in RAM, name node is also maintaining metadata in disk. Now, that is what we see in the red box, which basically has information of whatever information was written to HDFS. So to summarize, your name node has metadata in RAM and metadata in disk. Your data nodes are the machines where your blocks or data is actually getting stored. And then there is an auto replication feature, which is always existing unless and until you have disabled it, and your read and write activity is a parallel activity. However, replication is a sequential activity. Now, this is what I mentioned about when you talk about name node, which is the master process hosting metadata in disk and RAM. So when we talk about disk, it basically has a edit log, which is your transaction log, and your FS image, which is your file system image. Right from the time the cluster was started, this metadata in disk was existing, and this gets appended every time read, write, or any other operations happen on HDFS. Metadata in RAM is dynamically built every time the cluster comes up, which basically means that if your cluster is coming up, name node in the initial few seconds or few minutes would be in a safe mode, which basically means it is busy registering the information from data nodes. So name node is one of the most critical processes. If name node is down and if all other processes are running, you will not be able to access the cluster. Name node's metadata in disk is very important for name node to come up and maintain the cluster. Name node's metadata in RAM is basically for all or satisfying all your client requests. Now, when we look at data nodes, as I mentioned, data nodes hold the actual data blocks, and they are sending these block reports every 10 seconds. So the metadata in name node's RAM is constantly getting updated, and metadata in disk is also constantly getting updated based on any kind of write activity happening on the cluster. Now data node, which is storing the block, will also help in any kind of read activity whenever a client requests. So whenever a client or an application or an API would want to read the data, it would first talk to name node. Name node would look into its metadata on RAM and confirm to the client which machines could be reached to get to that data. That's where your client would try to read the data from HDFS, which is actually getting the data from data nodes. And that's how your read-write requests are satisfied. Now, what are the two types of metadata in name node server holds? As I mentioned earlier, metadata in disk, very important to remember, edit log and FS image. Metadata in RAM, which is information about your data nodes, files being split into blocks residing on data nodes, and file permissions. So I will share a very good link on this, and you can always look for more detailed information about your metadata. So you can search for HDFS metadata directories explained. Now this is from Hortonworks. However, it talks about the metadata in disk, which name node manages, and details about this. So have a look at this link if you are more interested in learning about metadata on disk. Coming back, let's look at the next question. What is the difference between federation and high availability? Now these are the features which were introduced in Hadoop version 2. Both of these features are about horizontal scalability of name node. So prior to version 2, the only possibility was that you could have one single master, which basically means that your cluster could become unavailable if name node would crash. So Hadoop version 2 introduced two new features, federation and high availability. However, high availability is a popular one. So when you talk about federation, it basically means any number of name nodes. So there is no limitation to the number of name nodes. Your name nodes are in a federated cluster, which basically means name nodes still belong to the same cluster, but they are not coordinating with each other. So whenever a write request comes in, one of the name node picks up that request and it guides that request for the blocks to be written on data nodes. But for this, your name node does not have to coordinate with other name node to find out if the block ID which was being assigned was the same one as assigned by other name node. So all of them belong to a federated cluster. They are linked via a cluster ID. So whenever an application or an API is trying to talk to cluster, it is always going via an cluster ID, and one of the name node would pick up the read activity or write activity or processing activity. So all the name nodes are sharing a pool of metadata in which each name node will have its own dedicated pool. And we can remember that by a term called namespace or name service. So this also provides high fault tolerance. Suppose your one name node goes down, it will not affect or make your cluster unavailable. You will still have your cluster reachable because there are other name nodes running and they are available. Now when it comes to heartbeats, all your data nodes are sending their heartbeats to all the name nodes, and all the name nodes are aware of all the data nodes. When you talk about high availability, this is where you would only have two name nodes. So you would have an active and you would have a standby. Now normally in any environment you would see a high availability setup with Zookeeper. So Zookeeper is a centralized coordination service. So when you talk about your active and standby name nodes, election of a name node to be made as active and taking care of an automatic failover is done by your Zookeeper. High availability can be set up without Zookeeper, but that would mean that an admin's intervention would be required to make a name node as active from standby or also to take care of failover. Now at any point of time in high availability, a active name node would be taking care of storing the edits about whatever updates are happening on HDFS, and it is also writing these edits to a shared location. Standby name node is the one which is constantly looking for these latest updates and applying to its metadata, which is actually a copy of whatever your active name node has. So in this way, your standby name node is always in sync with the active name node, and if for any reason active name node fails, your standby name node will take over and become the active. Remember, Zookeeper plays a very important role here. It's a centralized coordination service. One more thing to remember here is that in your high availability, secondary name node will not be allowed. So you would have an active name node, and then you will have a standby name node which will be configured on a separate machine, and both of these will be having access to a shared location. Now that shared location could be NFS or it could be a quorum of journal nodes. So for more information, refer to the tutorial where I have explained about HDFS, high availability and federation. Now let's look at some logical question here. So if you have an input file of 350 MB, which is obviously bigger than 128 MB, how many input splits would be created by HDFS? And what would be the size of each input split? So for this, you need to remember that by default, the minimum block size is 128 MB. Now that's customizable. If your environment has more number of larger files written on an average, then obviously you have to go for a bigger block size. If your environment has a lot of files being written, but these files are of smaller size, you could be okay with 128 MB. Remember, in Hadoop, every entity, that is your directory on HDFS, file on HDFS, and a file having multiple blocks, each of these are considered as objects. And for each object, Hadoop's name node's RAM 150 bytes is utilized. So if your block size is very small, then you would have more number of blocks, which would directly affect the name node's RAM. If you keep a block size very high, that will reduce the number of blocks. But remember, that might affect in processing, because processing also depends on splits. More number of splits, more the parallel processing. So setting of block size has to be done with consideration about your parallelism requirement and your name node's RAM which is available. Now coming to the question, if you have a file of 350 MB, that would be split into 3 blocks, and here 2 blocks would have 128 MB data, and the third block, although the block size would still be 128, it would have only 94 MB of data. So this would be the split of this particular file. Now let's understand about rack awareness. How does rack awareness work? Or why do we even have racks? So organizations always would want to place their nodes or machines in a systematic way. There can be different approaches. You could have a rack which would have machines running on the master processes, and the intention would be that this particular rack could have higher bandwidth, more cooling, dedicated power supply, top of rack switch, and so on. The second approach could be that you could have one master process running on one machine of every rack, and then you could have other slave processes running. Now, when you talk about your rack awareness, one thing to understand is that if your machines are placed within racks, and we are aware that Hadoop follows auto replication, the rule of replication in a rack aware cluster would be that you would never have all the replicas placed on the same rack. So if we look at this, if we have block A in blue color, you will never have all the 3 blue boxes in the same rack, even if they are on different nodes, because that makes it less fault tolerant. So you would have at least one copy of block which would be stored on a different rack on a different node. Now let's look at this. So basically here we are talking about replicas being placed in such a way. Now somebody could ask a question, can I have my block and its replicas spread across 3 racks? And yes, you can do that, but then in order to make it more redundant, you are increasing your bandwidth requirement. So the better approach would be 2 blocks on the same rack on different machines and 1 copy on a different rack. Now let's proceed. How can you restart name node and all daemons in Hadoop? So if you were working on an Apache Hadoop cluster, then you could be doing a start and stop using Hadoop daemon scripts. So there are these Hadoop daemon scripts which would be used to start and stop your Hadoop. And this is when you talk about your Apache Hadoop. So let's look at one particular file which I would like to show you more information here. And this talks about your different clusters. So let's look into this, and so let's look at the start and stop. And here I have a file. Let's look at this one, and this gives you highlights. So if you talk about Apache Hadoop, this is how the setup would be done. So you would have it download the Hadoop tar file, you would have to untar it, edit the config files, you would have to do formatting, and then start your cluster. And here I have said using scripts. So this is in case of Apache Hadoop, you could be using a start all script that internally triggers start DFS and start yarn. And these scripts, start DFS, internally would run Hadoop daemon multiple times based on your configs to start your different processes. Then your start yarn would run yarn daemon script to start your processing related processes. So this is how it happens in Apache Hadoop. Now in case of Cloudera or Hortonworks, which is basically a vendor specific distribution, you would have say multiple services which would have one or multiple daemons running across the machines. Let's take an example here that you would have machine 1, machine 2 and machine 3 with your processes spread across. However, in case of Cloudera and Hortonworks, these are cluster management solutions. So you would never be involved in running a script individually to start and stop your processes. In fact, in case of Cloudera, you would have a Cloudera SCM server running on one of the machines and then Cloudera SCM agents running on every machine. If you talk about Hortonworks, you would have Ambari server and Ambari agent running. So your agents which are running on every machine are responsible to monitor the processes, send also their heartbeat to the master, that is your server, and your server is the one or a service which basically will give instructions to the agents. So in case of vendor specific distribution, your start and stop of processes is automatically taken care by these underlying services, and these services internally are still running these commands. However, only in Apache Hadoop you have to manually follow these to start and stop. Coming back, we can look into some command related questions. So which command will help you find the status of blocks and file system health? So you can always go for a file system check command. Now that can show you the files for a particular HDFS path. It can show you the blocks, and it can also give you information on status such as under replicated blocks, over replicated blocks, misreplicated blocks, default replication, and so on. So your FSCK file system check utility does not repair if there is any problem with the blocks, but it can give you information of blocks related to the files, on which machines they are stored, if they are replicated as per the replication factor, or if there is any problem with any particular replica. Now, what would happen if you store too many small files in a cluster? And this relates to the block information which I gave some time back. So remember, Hadoop is coded in Java. So here every directory, every file and file related block is considered as an object. And for every object within your Hadoop cluster, name node's RAM gets utilized. So more number of blocks you have, more would be usage of name node's RAM. And if you're storing too many small files, it would not affect your disk. It would directly affect your name node's RAM. That's why in production clusters, admin guys or infrastructure specialists will take care that everyone who is writing data to HDFS follows a quota system, so that you could be controlled in the amount of data you write plus the count of data an individual writes on HDFS. Now, how do you copy data from local system onto HDFS? So you can use a put command or a copy from local, and then given your local path, which is your source, and then your destination, which is your HDFS path. Remember, you can always do a copy from local using a -f option. That's a flag option, and that also helps you in writing the same file or a new file to HDFS. So with your -f, you have a chance of overwriting or rewriting the data which is existing on HDFS. So copy from local or -put, both of them do the same thing, and you can also pass an argument when you're copying to control your replication or other aspects of your file. Now, when do you use DFS admin refresh nodes or RM admin refresh nodes? So as the command says, this is basically to do with refreshing the node information. So your refresh nodes is mainly used when, say, a commissioning or decommissioning of nodes is done. So when a node is added into the cluster or when a node is removed from the cluster, you are actually informing Hadoop master that this particular node would not be used for storage and would not be used for processing. Now in that case, you would be, once you are done with the process of commissioning or decommissioning, you would be giving these commands, that is refresh nodes and rmadmin refresh nodes. So internally, when you talk about commissioning, decommissioning, there are include and exclude files which are updated. And these include and exclude files will have entry of machines which are being added to the cluster or machines which are being removed from the cluster. And while this is being done, the cluster is still running. So you do not have to restart your master process. However, you can just use these refresh commands to take care of your commissioning, decommissioning activities. Now, is there any way to change replication of files on HDFS after they are already written? And the answer is, of course, yes. So if you would want to set a replication factor at a cluster level, and if you have admin access, then you could edit your HDFS-site file, or you could say Hadoop-site file. And that would take care of replication factor being set at a cluster level. However, if you would want to change the replication after the data has been written, you could always use a setrep command. So setrep command is basically to change the replication after the data is written. You could also write the data with a different replication, and for that you could use a -d dfs.replication and give your replication factor when you are writing data to the cluster. So in Hadoop, you can let your data be replicated as per the property set in the config file. You could write the data with a different replication. You could change the replication after the data is written. So all these options are available. Now, who takes care of replication consistency in a Hadoop cluster? And what do you mean by under, over replicated blocks? Now, as I mentioned, your fsck command can give you information of over or under replicated blocks. Now, in a cluster, it is always and always name node which takes care of replication consistency. So for example, if you have set up a replication of 3, and since we know the first rule of replication, which basically means that you cannot have 2 replicas residing on the same node, it would mean that if your replication is 3, we would need at least 3 data nodes available. Now say for example, you had a cluster with 3 nodes and replication was set to 3. At one point of time, one of your name node crashed. And if that happens, your blocks would be under replicated. That means there was a replication factor set, but now your blocks are not replicated, or there are not enough replicas as per the replication factor set. This is not a problem. Your master process or name node will wait for some time before it will start the replication of data again. So if a data node is not responding, or if a disk has crashed, and if name node does not get information of a replica, name node will wait for some time and then it will start re-replication of those missing blocks from the available nodes. However, while name node is doing it, the blocks are in under replicated situation. Now when you talk about over replicated, this is a situation where name node realizes that there are extra copies of block. Now this might be the case that you had 3 nodes running with a replication of 3. One of the node went down due to a network failure or some other issue. Within few minutes, name node re-replicated the data, and then the failed node is back with its set of blocks. Again, name node is smart enough to understand that this is a over replication situation, and it will delete set of blocks from one of the nodes. It might be the node which has been recently added, it might be your old node which has joined your cluster again, or any node. That depends on the load on a particular node. Now we discussed about Hadoop, we discussed about HDFS. Now we will discuss about MapReduce, which is the programming model, and you can say processing framework. what is distributed cache in MapReduce? Now we know that when we talk about MapReduce, the data which has to be processed might be existing on multiple nodes. So when you would have your MapReduce program running, it would basically read the data from the underlying disks. Now this could be a costly operation if every time the data has to be read from disk. So distributed cache is a mechanism wherein data set or data which is coming from the disk can be cached and available for all worker nodes. Now how will this benefit? So when a MapReduce is running, instead of every time reading the data from disk, it would pick up the data from distributed cache, and this will benefit your MapReduce processing. So distributed cache can be set in your job conf, where you can specify that a file should be picked up from distributed cache. Now let's understand about these roles. So what is a record reader, what is a combiner, what is a partitioner, and what kind of roles do they play in a MapReduce processing paradigm or MapReduce operation. So record reader communicates with the input split, and it basically converts the data into key value pairs. And these key value pairs are the ones which will be worked upon by the mapper. Your combiner is an optional phase. It's like a mini reduce. So combiner does not have its own class. It relies on the reducer class. Basically, your combiner would receive the data from your map tasks which would have completed, works on it based on whatever reducer class mentions, and then passes its output to the reducer phase. Partitioner is basically a phase which decides how many reduce tasks would be used, aggregate or summarize your data. So partitioner is a phase which would decide based on the number of keys, based on the number of map tasks. Your partitioner would decide if one or multiple reduce tasks would be used to take care of processing. So either it could be partitioner which decides on how many reduce tasks would run, or it could be based on the properties which we have set within the cluster, which will take care of the number of reduce tasks which would be used. Always remember, your partitioner decides how outputs from combiner are sent to reducer and to how many reducers. It controls the partitioning of keys of your intermediate map outputs. So map phase, whatever output it generates, is an intermediate output, and that has to be taken by your partitioner or by a combiner and then partitioner to be sent to one or multiple reduce tasks. This is one of the common questions which you might face. Why is MapReduce slower in processing? So we know MapReduce goes for parallel processing. We know we can have multiple map tasks running on multiple nodes at the same time. We also know that multiple reduce tasks could be running. Now why does then MapReduce become a slower approach? First of all, your MapReduce is a batch oriented operation. Now MapReduce is very rigid and it strictly uses mapping and reducing phases. So no matter what kind of processing you would want to do, you would have to still provide the mapper function and the reducer function to work on data. Not only this, whenever your map phase completes, the output of your map phase, which is an intermittent output, would be written to HDFS and thereafter underlying disks. And this data would then be shuffled and sorted and picked up for reducing phase. So every time your data being written to HDFS and retrieved from HDFS makes MapReduce a slower approach. The question is, for a MapReduce job, is it possible to change the number of mappers to be created? Now, by default, you cannot change the number of map tasks because number of map tasks depends on the input splits. However, there are different ways in which you can either set a property to have more number of map tasks which can be used, or you can customize your code or make it use a different format which can then control the number of map tasks. By default, number of map tasks are equal to the number of splits of file you are processing. So if you have a 1 GB of file that is split into 8 blocks of 128 MB, there would be 8 map tasks running on the cluster. These map tasks are basically running your mapper function. If you have hard-coded properties in your mapred-site file to specify more number of map tasks, then you could control the number of map tasks. Let's also talk about some data types. So when you prepare for Hadoop, when you want to get into big data field, you should start learning about different data formats. Now there are different data formats such as Avro, Parquet, you have sequence file or binary format, and these are different formats which are used. Now when you talk about your data types in Hadoop, these are implementation of your writable and writable comparable interfaces. So for every data type in Java, you have a equivalent in Hadoop. So int in Java would be int writable in Hadoop, float would be float writable, long would be long writable, double writable, boolean writable, array writable, map writable, and object writable. So these are your different data types that could be used within your MapReduce program. And these are implementation of writable and writable comparable interfaces. What is speculative execution? Now imagine you have a cluster which has huge number of nodes and your data is spread across multiple slave machines or multiple nodes. Now at a point of time, due to a disk degrade or network issues or machine heating up or more load being on a particular node, there can be a situation where your data node will execute task in a slower manner. Now in this case, if speculative execution is turned on, there would be a shadow task or another similar task running on some other node for the same processing. So whichever task finishes first will be accepted and the other task would be killed. So speculative execution could be good if you are working in an intensive workload kind of environment, where if a particular node is slower, you could benefit from a unoccupied or a node which has less load to take care of your processing. Going further, this is how we can understand. So node A, which might be having a slower task, you would have a scheduler which is maintaining or having knowledge of what are the resources available. So if speculative execution as a property is turned on, then the task which was running slow, a copy of that task, or you can say a shadow task, would run on some other node, and whichever task completes first will be considered. This is what happens in your speculative execution. Now, how is identity mapper different from chain mapper? Now, this is where we are getting deeper into MapReduce concepts. So when you talk about mapper, identity mapper is the default mapper which is chosen when no mapper is specified in MapReduce driver class. So for every MapReduce program, you would have a map class which is taking care of your mapping phase, which basically has a mapper function and which would run one or multiple map tasks, right? Your program would also have a reduce class which would be running a reducer function which takes care of reduce tasks running on multiple nodes. Now if a mapper is not specified within your driver class, so driver class is something which has all information about your flow. What's your map class? What is your reduce class? What's your input format? What's your output format? What are the job configurations, and so on. So identity mapper is the default mapper which is chosen when no mapper class is mentioned in your driver class. It basically implements an identity function which directly writes all its key pairs into output, and it was defined in old MapReduce API in this particular package. But when you talk about chaining mappers or chain mapper, this is basically a class to run multiple mappers in a single map task. Or basically you could say multiple map tasks would run as a part of your processing. The output of first mapper would become as an input to second mapper, and so on. And this can be defined in the undermentioned class or package. What are the major configuration parameters required in a MapReduce program? Obviously, we need to have the input location. We need to have the output location. So input location is where the files will be picked up from, and this would preferably on HDFS directory. Output location is the path where your job output would be written by your MapReduce program. You also need to specify input and output formats. If you don't specify, the defaults are considered. Then we need to also have the classes which have your map and reduce functions. And if you intend to run the code on a cluster, you need to package your class in a jar file, export it to your cluster, and then this jar file would have your mapper, reducer, and driver classes. So these are important configuration parameters which you need to consider for a MapReduce program. Now, what is the difference, or what do you mean by map side join and reduce side join? Map side join is basically when the join is performed at the mapping level or at the mapping phase, or is performed by the mapper. So each input data which is being worked upon has to be divided into same number of partitions. Input to each map is in the form of a structured partition and is in sorted order. So map side join, you can understand it in a simpler way, that if you compare it with RDBMS concepts where you had two tables which were being joined, it will always be advisable to give your bigger table as the left side table or the first table for your join condition, and it would be your smaller table on the left side and your bigger table on the right side, which basically means the smaller table could be loaded in memory and could be used for joining. So map side join is a similar kind of mechanism where input data is divided into same number of partitions. When you talk about reduce side join, here the join is performed by the reducer. So it is easier to implement than map side join, as all the sorting and shuffling will send the values, or send all the values having identical keys to the same reducer. So you don't need to have your data set in a structured form. So look into your map side join or reduce side join and other joins just to understand how MapReduce works. However, I would suggest not to focus more on this, because MapReduce is still being used for processing, but the amount of MapReduce based processing has decreased overall or across the industry. Now, what is the role of output committer class in a MapReduce job? So output committer, as the name says, describes the commit of task output for a MapReduce job. So we could have this as mentioned: org Apache Hadoop MapReduce output committer. You could have a class which extends your output committer class. So MapReduce relies on this. MapReduce relies on the output committer of the job to set up the job initialization, cleaning up the job after the job completion. That means all the resources which were being used by a particular job, setting up the task temporary output, checking whether a task needs a commit, committing the task output, and discarding the task out. So this is a very important class and can be used within your MapReduce job. What is the process of spilling in MapReduce? What does that mean? So spilling is basically a process of copying the data from memory buffer to disk when obviously the buffer usage reaches a certain threshold. So if there is not enough memory in your buffer, in your memory, then the content which is stored in buffer or memory has to be flushed out. So by default, a background thread starts spilling the content from memory to disk after 80% of buffer size is filled. Now, when is the buffer being used? So when your MapReduce processing is happening, the data is being read from the disk, loaded into the buffer, and then some processing happens. Same thing also happens when you are writing data to the cluster. So you can imagine, for a 100 megabyte size buffer, the spilling will start after the content of buffer reaches 80 megabytes. This is customizable. How can you set the mappers and reducers for a MapReduce job? So these are the properties. So number of mappers and reducers, as I mentioned earlier, can be customized. So by default, your number of map tasks depends on the split, and number of reduced tasks depends on the partitioning phase, which decides number of reduced tasks which would be used depending on the keys. However, we can set these properties either in the config files or provide them on the command line, or also make them part of our code, and this can control the number of map tasks or reduced tasks which would be run for a particular job. Let's look at one more interesting question. What happens when a node running a map task fails before sending the output to the reducer? So there was a node which was running a map task, and we know that there could be one or multiple map tasks running on one or multiple nodes, and all the map tasks have to be completed before the further stages that such as combiner or reducer come into existence. So in a case if a node crashes where a map task was assigned to it, the whole task will have to be run again on some other node. So in Hadoop version 2, Yarn framework has a temporary daemon called application master. So your application master is taking care of execution of your application. And if a particular task on a particular node failed due to unavailability of node, it is the role of application master to have this task scheduled on some other node. Now, can we write the output of MapReduce in different formats? Of course we can. So Hadoop supports various input and output formats. So you can write the output of MapReduce in different formats. So you could have the default format, that is text output format, wherein records are written as line of text. You could have sequence file, which is basically to write sequence files or your binary format files, where your output files need to be fed into another MapReduce jobs. You could go for a map file output format to write output as map files. You could go for a sequence file as a binary output format. So that's again a variant of your sequence file input format. It basically writes keys and values to a sequence file. So when we talk about binary format, we are talking about a non-human readable format. DB output format. Now, this is basically used when you would want to write data to, say, relational databases or, say, NoSQL databases such as HBase. So this format also sends the reduce output to a SQL table. Now, let's learn a little bit about Yarn. Yarn, which stands for yet another resource negotiator. It's the processing framework. So what benefits did Yarn bring in Hadoop version 2, and how did it solve the issues of MapReduce version 1? So MapReduce version 1 had major issues when it comes to scalability or availability because, in Hadoop version 1, you had only one master process for processing layer, and that is your job tracker. So your job tracker was listening to all the task trackers which were running on multiple machines. So your job tracker was responsible for resource tracking and job scheduling. In Yarn, you still have a processing master, but that's called resource manager instead of job tracker. And now with Hadoop version 2, you could even have resource manager running in high availability mode. You have node managers which would be running on multiple machines, and then you have a temporary daemon called application master. So in case of Hadoop version 2, your resource manager or master is only handling the client connections and taking care of tracking the resources. The jobs scheduling, or basically taking care of execution across multiple nodes, is controlled by application master till the application completes. So in Yarn, you can have different kind of resource allocations that could be done, and there is a concept of container. So container is basically a combination of RAM and CPU cores. Yarn can run different kind of workloads. So it is not just MapReduce kind of workload which can be run on Hadoop version 2, but you could have graph processing, massive parallel processing, you could have real-time processing, and huge processing applications could run on a cluster based on Yarn. So when we talk about scalability, in case of your Hadoop version 2, you can have a cluster size of more than 10,000 nodes and can run more than 100,000 concurrent tasks. And this is because for every application which is launched, you have this temporary daemon called application master. So if I would have 10 applications running, I would have 10 app masters running, taking care of execution of these applications across multiple nodes. Compatibility. So Hadoop version 2 is fully compatible with whatever was developed as per Hadoop version 1, and all your processing needs would be taken care by Yarn. So dynamic allocation of cluster resources, taking care of different workloads, allocating resources across multiple machines and using them for execution, all that is taken care by Yarn. Multi-tenancy, which basically means you could have multiple users or multiple teams. You could have open source and proprietary data access engines, and all of these could be basically hosted using the same cluster. Now, how does Yarn allocate resources to an application with the help of its architecture? So basically, you have a client or an application or an API which talks to Resource Manager. Resource Manager is, as I mentioned, managing the resource allocation in the cluster. When you talk about Resource Manager, you have its internal two components. One is your scheduler and one is your applications manager. So when we say Resource Manager being the master is tracking the resources, Resource Manager is the one which is negotiating the resources with slave. It is not actually Resource Manager who is doing it, but these internal components. So you have a scheduler which allocates resources to various running applications. So scheduler is not bothered about tracking your resources or basically tracking your applications. So we can have different kind of schedulers such as FIFO, which is first in first out. You could have a fair scheduler or you could have a capacity scheduler. And these schedulers basically control how resources are allocated to multiple applications when they are running in parallel. So there is a queue mechanism. So scheduler will schedule resources based on requirements of application, but it is not monitoring or tracking the status of applications. Your applications manager is the one which is accepting the job submissions. It is monitoring and restarting the application masters. So it's application manager which is basically then launching a application master which is responsible for an application. So this is how it looks. So whenever a job submission happens, we already know that resource manager is aware of the resources which are available with every node manager. So on every node which has fixed amount of RAM and CPU cores, some portion of resources, that is your RAM and CPU cores, are allocated to node manager. Now resource manager is already aware of how much resources are available across nodes. So whenever a client request comes in, resource manager will make a request to node manager. It will basically request node manager to hold some resources for processing. Node manager would basically approve or disapprove this request of holding resources. And these resources, that is a combination of RAM and CPU cores, are nothing but containers. We can allocate containers of different sizes within yarn-site file. So your node manager, based on a request from resource manager, guarantees the container which would be available for processing. That's when your resource manager starts a temporary daemon called application master to take care of your execution. So your app master, which was launched by resource manager, or we can say internally by applications manager, will run in one of the containers, because application master is also a piece of code. So it will run in one of the containers and then other containers will be utilized for execution. This is how Yarn is basically taking care of your allocation. Your application master is managing resource needs. It is the one which is interacting with scheduler, and if a particular node crashes, it is the responsibility of app master to go back to the master, which is resource manager, and negotiate for more resources. So your app master will never ever negotiate resources with node manager directly. It will always talk to resource manager, and resource manager is the one which negotiates the resources. Container, as I said, is a collection of resources like your RAM, CPU, network bandwidth, and your container is allocated based on the availability of resources on a particular node. So, which of the following has occupied the place of a job tracker of MapReduce? So it is your resource manager. So resource manager is the name of the master process in Hadoop version 2. Now, if we would have to write yarn commands to check the status of an application, so we could just say yarn application minus status and then the application ID. And you could kill it also from the command line. Remember, your yarn has a UI, and you can even look at your applications from the UI. You can even kill your applications from the UI. However, knowing the command line commands would be very useful. Can we have more than one resource manager in a yarn based cluster? Yes, we can. That is what Hadoop version 2 allows us to have. So you can have a high availability yarn cluster where you have an active and standby, and the coordination is taken care by your Zookeeper. At a particular time, there can only be one active resource manager. And if active resource manager fails, your standby resource manager comes and becomes active. However, Zookeeper is playing a very important role. Remember, Zookeeper is the one which is coordinating the server state, and it is doing the election of active to standby failover. What are the different schedulers available in Yarn? So you have a FIFO scheduler, that is first in, first out. And this is not a desirable option because in this case, a longer running application might block all other small running applications. Your capacity scheduler is basically a scheduler where dedicated queues are created and they have fixed amount of resources. So you can have multiple applications accessing the cluster at the same time, and they would be using their own queues and the resources allocated to them. If you talk about fair scheduler, you don't need to have a fixed amount of resources. You can just have a percentage and you could decide what kind of fairness is to be followed, which basically means that if you were allocated 20 gigabytes of memory, however, the cluster has 100 gigabytes and the other team was assigned 80 gigabytes of memory, then you have 20% access to the cluster, another team has 80%. However, if the other team does not come up or does not use the cluster, in a fair scheduler, you can go up to maximum of 100% of your cluster. To find out more information about your schedulers, you could either look in Hadoop definitive guide, or what you could do is you could just go to Google and you could type, for example, yarn scheduler. Let's search for yarn scheduler, and then you can look in Hadoop definitive guide. And so this is your Hadoop definitive guide, and it beautifully explains about your different schedulers, how do multiple applications run, and that could be in your FIFO kind of scheduling, it could be in capacity scheduler, or it could be in a fair scheduling. So have a look at this link. It's a very good link. You can also search for yarn untangling, and this is a blog of this is a series of 4 blogs where it's beautifully explained about your yarn, how it works, how the resource allocation happens, what is a container, and what runs within the container. So you can scroll down, you can be reading through this, and you can then also search for part 2 of it, which talks about allocation and so on. So coming back, we basically have these schedulers. What happens if a resource manager fails while executing an application in a high availability cluster? So in a high availability cluster, we know that we would have 2 resource managers, one being active, one being standby, and Zookeeper, which is keeping a track of the server states. So if a RM fails in case of high availability, the standby will be elected as active, and then basically your resource manager or the standby would become the active one. And this one would instruct the application master to abort in the beginning. Then your resource manager recovers its running state. So there is something called as RM state store, where all the applications which are running, their status is stored. So resource manager recovers its running state by looking at your state store, by taking advantage of container statuses, and then continues to take care of your processing. Now, in a cluster of 10 data nodes, each having 16 GB and 10 cores, what would be total processing capacity of the cluster? Take a minute to think. 10 data nodes, 16 GB RAM, per node 10 cores. So, if you mention the answer as 160 GB RAM and 100 cores, then you went wrong. Now think of a cluster which has 10 data nodes, each having 16 GB RAM and 10 cores. Remember, on every node in a Hadoop cluster, you would have one or multiple processes running. Those processes would need RAM. The machine itself, which has a Linux file system, would have its own processes. So that would also be having some RAM usage, which basically means that if you talk about 10 data nodes, you should deduct at least 20 to 30% towards the overheads, towards the cloud database services, towards the other processes which are running. And in that case, I could say that you could have 11 or 12 GB available on every machine for processing and say 6 or 7 cores. Multiply that by 10 and that's your processing capacity. Remember, the same thing applies to the disk usage also. So if somebody asks you in a 10 data node cluster where each machine has 20 terabytes of disks, what is my total storage capacity available for HDFS? So the answer would not be 200. You have to consider the overheads. And this is basically which gives you your processing capacity. Now let's look at one more question. So what happens if requested memory or CPU cores beyond or goes beyond the size of container? Now, as I said, you can have your configurations which can say that in a particular data node which has 100 GB RAM, I could allocate say 50 GB for the processing. Out of 100 cores, I could say 50 cores for processing. So if you have 100 GB RAM and 100 cores, you could ideally allocate 100 for processing, but that's not ideally possible. So if you have 100 GB RAM, you would go for 50 GB, and if you have 100 cores, you would go for 50 cores. Now, within this RAM and CPU cores, you have the concept of containers, right? So container is a combination of RAM and CPU cores. So you could have a minimum size container and maximum size container. Now, at any point of time, if your application starts demanding more memory or more CPU cores, and this cannot fit into a container allocation, your application will fail. Your application will fail because you requested for a memory or a combination of memory and CPU cores which is more than the maximum container size. Now here we will discuss on Hive, Pig, HBase, and these components of Hadoop which are being used in the industry for various use cases. Let's look at some questions here and let's look how you should prepare for them. So first of all, we will learn on Hive, which is a data warehousing package. So the question is, what are the different components of a Hive architecture? Now, when we talk about Hive, we already know that Hive is a data warehousing package, which basically allows you to work on structured data or data which can be structurized. So normally people are well versed with querying or basically processing the data using SQL queries. A lot of people come from database backgrounds and they would find it comfortable if they know structured query language. Hive is one of the data warehousing package which resides within a Hadoop ecosystem. It uses Hadoop's distributed file system to store the data, and it uses RDBMS usually to store the metadata, although metadata can be stored locally also. So what are the different components of an Hive architecture? So it has a user interface. So user interface calls the execute interface to the driver. This creates a session to the query, and then it sends the query to the compiler to generate an execution plan for it. Usually, whenever Hive is set up, it would have its metadata stored in an RDBMS. Now, to establish the connection between RDBMS and Hadoop, we need ODBC or JDBC connector jar file, and that connector jar file has a driver class. Now this driver class is mandatory to create a connection between Hive and Hadoop. So user interface creates this interface using the driver. Now we have Metastore. Metastore stores the metadata information. So any object which you create, such as database, table, indexes, their metadata is stored in Metastore, and usually this Metastore is stored in an RDBMS so that multiple users can connect to Hive. So your Metastore stores the metadata information and sends that to the compiler for execution of a query. What does the compiler do? It generates the execution plan. It has a DAG. Now DAG stands for direct acyclic graph. So it has a DAG of stages where each stage is either a metadata operation, a MapReduce job, or an operation on HDFS. And finally, we have execution engine that acts as a bridge between Hive and Hadoop to process the query. So execution engine communicates bidirectionally with Metastore to perform operations like create or drop tables. So these are four important components of Hive architecture. Now, what is the difference between external table and managed table in Hive? So we have various kinds of table in Hive, such as external table, managed table, partition table. The major difference between your managed and external table is in respect to what happens to the data if the table is dropped. Usually whenever we create a table in Hive, it creates a managed table, or we could also call that as an internal table. Now this manages the data and moves it into warehouse directory by default. Whether you create a managed table or external table, usually the data can reside in Hive's default warehouse directory, or it could be residing in a location chosen. However, when we talk about managed table, if one drops a managed table, not only the metadata information is deleted, but the table's data is also deleted from HDFS. If we talk about external table, it is created with an external keyword explicitly, and if an external table is dropped, nothing happens to the data which resides in HDFS. So that's the main difference between your managed and external table. What might be the use case if somebody asks you? There might be a migration kind of activity, or you are interested in creating a lot of tables using your queries. So in that case, you could dump all the data on HDFS, and then you could create a table by pointing to a particular directory or multiple directories. Now you could then do some testing of your tables and would decide that you might not need all the tables. So in that case, it would be advisable to create external tables so that even if the table is later dropped, the data on HDFS will be intact, unlike your managed table where dropping of table will delete the data from HDFS also. Let's learn a little bit on partition. So what is partition in Hive and why is partitioning required in Hive? If somebody asks you that. Now, normally in world of RDBMS, partition is the process to group similar type of data together. And that is usually done on basis of a column or what we call as partitioning key. Now, each table usually has one column in context of RDBMS, which could be used to partition the data. And why do we do that? So that we can avoid scanning the complete table for a query and restrict the scan to set of data or to a particular partition. In Hive, we can have any number of partition keys. So partitioning provides granularity in Hive table. It reduces the query latency by scanning only relevant partition data instead of whole data set. We can partition at various levels. Now, if I compare RDBMS with Hive, in case of RDBMS, you could have one column which could be used for partitioning, and then you could be querying the specific partition. So in case of RDBMS, your partition column is usually a part of the table definition. So for example, if I have an employee table, I might have employee ID, employee name, employee age, and employee salary as 4 columns, and I would decide to partition the table based on salary column. Now, why would I partition it? Because I feel that employee table is growing very fast. It is, or it will have huge amount of data. And later when we query the table, we don't want to scan the complete table. So I could split my data into multiple partition based on a salary column giving some ranges. In Hive, it is a little different. In Hive, you can do partitioning, and there is a concept of static and dynamic partitioning. But in Hive, the partition column is not part of table definition. So you might have an employee table with employee ID, name, age, and that's it. That would be the table definition. But you could then have partitioning done based on salary column, which will then create a specific folder on HDFS. In that case, when we query the data, we can see the partition column also showing up. So we can partition the transaction data for a bank, for example, based on month like Jan, Feb, etc. And any operation regarding a particular month will then allow us to query that particular folder. That is where partitioning is useful. Now, why does Hive not store metadata information in HDFS if somebody asks you? So we know that Hive's data is stored in HDFS, which is Hadoop distributed file system. However, the metadata is either stored locally, and that mode of Hive would be called as embedded mode, or you could have Hive's metadata stored in RDBMS so that multiple clients can initiate a connection. Now this metadata, which is very important for Hive, would not be stored in HDFS. So we already know that HDFS read and write operations are time consuming. It is a distributed file system and it can accommodate huge amount of data. So Hive stores metadata information in metastore using RDBMS instead of HDFS. So this allows to achieve low latency and faster data access. Now, if somebody asks, what are the components used in Hive query processor? So usually we have the main components are your parser, your execution engine, logical plan generation, optimizer, and type checking. So whenever a query is submitted, it will go through a parser, and parser would check the syntax, it would check for objects which are being queried and other things to see if the query is fine. Now internally you have a semantic analyzer which will also look at the query. You have an execution engine which basically will work on the execution part. That is the best generated execution plan which could be used to get the results for the query. You could also have user-defined functions which a user would want to use, and these are normally created in Java or Java programming language, and then basically these user-defined functions are added to the class path. Now you would have a logical plan generation which basically looks at your query and then generates a logical plan or the best execution path which would be required to get to the results. Internally, there is a physical plan generated, which is then looked in by optimizer to get the best path to get to the data. And that might also be checking your different operators which you are using within your query. Finally, we would also have type checking. So these are important components in Hive. So somebody might ask you, if you are querying your data using Hive, what are the different components involved? Or if you could explain what are the different components which work when a query is submitted. So these are the components. Now let's look a scenario-based question. Suppose there are a lot of small CSV files which are present in a HDFS directory, and you want to create a single Hive table from these files. So data in these files have fields like registration number, name, email, address. So if this is what needs to be done, what will be your approach to solve it? Where will you create a single Hive table for lots of small files without degrading the performance of the system? So there can be different approaches. Now we know that there are a lot of small CSV files which are present in a directory. So we know that when we create a table in Hive, we can use a location parameter. So I could say create table, give a table name, give the column and their data types. I could specify the delimiters, and finally I could say location and then point it to a directory on HDFS. And this directory might be the directory which has a lot of CSV files. So in this case, I will avoid loading the data in the table, because table pointing to the directory will directly pick up the data from one or multiple files. And we also know that Hive does schema check on read. So it does not do a schema check on write. So in case there were one or two files which did not follow the schema of the table, it would not prevent data loading. Data would anyways be loaded. Only when you query the data, it might show you null values if data which was loaded does not follow the schema of the table. This is one approach. What is the other approach? So let's look at that. You can think about sequence file format, which is basically a smart format or a binary format, and you can group these small files together to form a sequence file. Now this could be one other smarter approach. So we could create a temporary table. So we could say create table, give a table name, give the column names and their data types. We could specify the delimiters as it shows here, that is row format, and fields terminated by. And finally, we can store that as text file. Then we can load data into this table by giving a local file system path. And then we can create a table that will store data in sequence file format. So my point 1 is storing the data in text file. Point 3 would be storing the data in sequence file format. So we say create table, give the specifications, we say row format delimited, fields are terminated by comma, stored as sequence file. Then we can move the data from test table into test sequence file table. So I could just say insert overwrite my new table as select star from other table. Remember, in Hive, you cannot do insert, update, delete. However, if the table is existing, you can do a insert overwrite from an existing table into a new table. So this could be one approach where we could have a lot of CSV files or smaller files clubbed together as one big sequence file and then store it in the table. Now, if somebody asks you, write a query to insert a new column, that is integer data type, into a Hive table, and the requirement might be that you would want to insert this table at a position before an existing column. Now that's possible by doing an alter table, giving your table name, and then specifying change column, giving your new column with the data type before an existing column. This is a simple way wherein you can insert a new column into a Hive table. What are the key differences between Hive and Pig? Now, some of you might have heard Hive is a data warehousing package and Pig is more of a scripting language. Both of them are used for data analysis, trend detection, hypothesis testing, data transformation, and many other use cases. So if we compare Hive and Pig, Hive uses a declarative language called HiveQL, that is Hive querying language, similar to SQL, and it is for reporting or for data analysis, even for data transformation or for your data extraction. Pig uses a high-level procedural language called Pig Latin for programming. Both of them, remember, use MapReduce processing framework. So when we run a query in Hive to process the data, or when we create and submit a Pig script, both of them trigger a MapReduce job unless and until we have set them to local mode. Hive operates on the server side of the cluster and basically works on structured data or data which can be structurized. Pig usually works or operates on the client side of the cluster and allows both structured, unstructured, or even I could say semi-structured data. Hive does not support Avro file format by default. However, that can be done by using the write serializer deserializer. So we can have Hive table related data stored in Avro format, in sequence file format, in Parquet format, or even as a text file format. However, when we are working on smarter formats like Avro or sequence file or Parquet, we might have to use specific serializers, deserializers. For Avro, this is the package which allows us to use Avro format. Pig supports Avro format by default. Hive was developed by Facebook and it supports partitioning, and Pig was developed by Yahoo and it does not support partitioning. So these are high-level differences. There are lots and lots of differences. Remember, Hive is more of a data warehousing package and Pig is more of a scripting language or a strictly procedural flow following scripting language which allows us to process the data. Now let's get more deeper and learn about Pig, which is, as I mentioned, a scripting language which can be used for your data processing. It also uses MapReduce, although we can even have Pig run in a local mode. Let's learn about Pig in the next section. Now let's learn on some questions about Pig, which is a scripting language and it is extensively used for data processing and data analysis. So the question is, how is Apache Pig different from MapReduce? Now we all know that MapReduce is a programming model. It's quite rigid when it comes to processing the data because you have to do the mapping and reducing. You have to write huge code. Usually MapReduce is written in Java, but now it can also be written in Python. It can be written in Scala and other programming languages. So if we compare Pig with MapReduce, Pig obviously is very concise. It has less lines of code when compared to MapReduce. Now, we also know that Pig script internally will trigger a MapReduce job. However, user need not know about MapReduce programming model. They can simply write simple scripts in Pig and that will automatically be converted into MapReduce. However, MapReduce has more lines of code. Pig is high-level language which can easily perform join operations or other data processing operations. MapReduce is a low-level language which cannot perform join operations easily. So we can do join using MapReduce. However, it's not really easy in comparison to Pig. Now, as I said, on execution, every Pig operator is converted internally into a MapReduce job. So every Pig script which is run, which would be converted into MapReduce job. Now, MapReduce overall is a batch-oriented processing, so it takes more time to compile, it takes more time to execute, either when you run a MapReduce job or when it is triggered by Pig script. Pig works with all versions of Hadoop, and when we talk about MapReduce program, which is written in one Hadoop version, may not work with other versions. It might work or it might not. It depends on what are the dependencies, what is the compiler you're using, what programming language you have used, and what version of Hadoop you are working on. So these are the main differences between Apache Pig and MapReduce. What are the different ways of executing Pig script? So you could create a script file, store it in .pig or .text, and then you could execute it using the pig command. You could be bringing up the grunt shell, that is Pig's shell. Now that usually starts with MapReduce mode, but then we can also bring it up in a local mode, and we can also run Pig embedded as an embedded script in other programming language. So these are the different ways of executing your Pig script. Now, what are the major components of Pig execution environment? This is a very common question. Interviewers would always want to know different components of Hive, different components of Pig, even different components which are involved in Hadoop ecosystem. So when we want to learn about major components of Pig execution environment, here are some. So you have Pig scripts. Now that is written in Pig Latin using built-in operators and user-defined functions and submitted to the execution environment. That's what happens when you would want to process the data using Pig. Now there is a parser which does type checking and checks the syntax of the script. The output of parser is a DAG, direct acyclic graph. So look in Wikipedia for DAG. So DAG is basically a sequence of steps which run in one direction. Then you have an optimizer. Now this optimizer performs optimization using merge, transform, split, etc. It aims to reduce the amount of data in the pipeline. That's the whole purpose of optimizer. You have a internal compiler. So Pig compiler converts the optimized code into a MapReduce job. And here user need not know the MapReduce programming model or how it works or how it is written. They all need to know about running the Pig script, which would be internally converted into a MapReduce job. And finally, we have an execution engine. So MapReduce jobs are submitted to the execution engine to generate the desired results. So these are major components of Pig execution environment. Now, let's learn about different complex data types in Pig. Pig supports various data types. The main ones are tuple, bag, and map. What is tuple or tuple? As you might have heard, a tuple is an ordered set of fields which can contain different data types for each field. So in array, you would have multiple elements, but that would be of same types. List can also have different types. Your tuple is a collection which has different fields, and each field can be of different type. Now we could have an example as 1, 3 or 1, 3, a string or a float element, and all of that form a tuple. Bag is a set of tuples. So that's represented by curly braces. So you could also imagine this like a dictionary which has various different collection elements. What is a map? Map is a set of key value pairs used to represent data. So when you work in big data field, you need to know about different data types which are supported by Pig, which are supported by Hive, which are supported in other components of Hadoop. So tuple, bag, map, array, array buffer, you can think about list, you can think about dictionaries, you can think about map, which is key value pair. So these are your different complex data types other than the primitive data types such as integer, character, string, boolean, float, and so on. Now, what are the various diagnostic operators available in Apache Pig? So these are some of the operators or options which you can give in a Pig script. You can do a dump. Now, dump operator runs the Pig Latin scripts and displays the result on the screen. So either I could do a dump and see the output on the screen, or I can even do a dump into and I could store my output in a particular file. So we can load the data using load operator in Pig. And then Pig also has different internal storage like JSON loader or Pig storage, which can be used if you're working on specific kind of data. And then you could do a dump either before processing or after processing, and dump would produce the result. The result could be stored in a file or seen on the screen. You also have a describe operator. Now that is used to view the schema of a relation. So you can load the data and then you can view the schema of relation using describe operator. Explain, as we might already know, displays the physical, logical, and MapReduce execution plans. So normally in RDBMS, when we use explain, we would like to see what happens behind the scenes when a particular script or a query runs. So we could load the data using load operator as in any other case. And if we would want to display the logical, physical, and MapReduce execution plans, we could use explain operator. There is also an illustrate operator. Now that gives the step-by-step execution of sequence of statements. So sometimes when we would want to analyze our script to see how good or bad they are, or would that really serve our purpose, we could use illustrate. And again, you can test that by loading the data using load operator, and you could just use a illustrate operator to have a look at the step-by-step execution of the sequence of statements which you would want to execute. So these are different diagnostic operators available in Apache Pig. Now, if somebody asks, state the usage of group, order by, and distinct keywords in Pig script. So as I said, Pig is a scripting language. So you could use various operators. So group basically collects various records with the same key and groups the data in one or more relations. Here is an example. You could do a group data. So that is basically a variable, or you can give some other name and you can say group relation name by age. Now say I have a file where I have various fields, and one of the field is a relation name. So I could group that by a different field. Order by is used to display the contents of relation in a sorted order, whether ascending or descending. So I could create a variable called relation2, and then I could say order relation name 1 by ascending or descending order. Distinct basically removes the duplicate records, and it is implemented only on entire records, not on individual records. So if you would want to find out the distinct values and relation name field, I could use distinct. What are the relational operators in Pig? So you have various relational operators which help data scientists or data analysts or developers who are analyzing the data, such as cogroup, which joins two or more tables and then performs group operation on the join table result. You have cross. It is used to compute the cross product, that is a Cartesian product of two or more relations. For each is basically to do some iteration. So if it will iterate through tuples of a relation, generating a data transformation. So for example, if I say variable A equals, and then I load a file in A, and then I could create a variable called B, where I could say for each A, I would want to do something, say group. Join is to join two or more tables in a relation. Limit is to limit the number of output tuples or output results. Split is to split the relation into two or more relations. Union is to get a combination, that's it will merge the contents of two or more relations. And order is to get a sorted result. So these are some relational operators which are extensively used in Pig for analysis. What is the use of having filters in Apache Pig? Now, say for example, I have some data which has three fields: year, product, quantity, and this is my phone sales data. So filter operator could be used to select the required values from a relation based on a condition. It also allows you to remove unwanted records from data file. So for example, filter the products where quantity is greater than 1000. So I see that I have one row wherein, or multiple rows where the quantity is greater than 1000, such as 1500, 1700, 1200. So I could create a variable called A. I would load my file using pig storage. As I explained earlier, pig storage is an internal parameter which can be used to specify the delimiters. Now here my delimiter is comma, so I could say using pig storage as, and then I could specify the data type for each field. So year being integer, product being character array, and quantity being integer. Then B, I could say filter A, whatever we have in A, by quantity greater than 1000. So it's very concise, it's very simple, and it allows us to extract and process data in a simpler way. Now, suppose there is a file called test.txt having 150 records in HDFS. So this is a file which is stored on HDFS and it has 150 records, where we can consider every record being one line. And if somebody asks you to write a pig command to retrieve the first 10 records of the file, first we will have to load the data. So I could create a variable called test_data, and I would say load my file using pig storage, specifying the delimiter as comma, as, and then I could specify my fields, whatever fields our file have. And then I would want to get only 10 records, for which I could use the limit operator. So I could say limit on test data and give me 10 records. This is very simple, and we can extract 10 records from 150 records which are stored in the file on HDFS. Now, we have learned on pig, we have learned some questions on Hive. You could always look more in books like Programming in Hive or Programming in Pig and look for some more examples and try out these examples on a existing Hadoop setup. Now let's learn on HBase, which is a NoSQL database. Now HBase is a 4-dimensional database in comparison to your RDBMS, which usually are 2-dimensional. So RDBMS have rows and columns, but HBase has 4 coordinates. It has row key, which is always unique, column family, which can be any number, column qualifiers, which can again be any number per column family, and then you have a version. So these 4 coordinates make HBase a 4-dimensional key value store or a column family store, which is unique for storing huge amount of data and extracting data from HBase. There is a very good link which I would suggest everyone can look at if you would want to learn more on HBase, and you could just say HBase mapper. And this basically brings up a documentation which is from MapR, but then that's not specific to MapR. And you can look at this link, which will give you a detailed explanation of HBase, how it works, what are the architectural components, and how data is stored, and how it makes HBase a very powerful NoSQL database. So let's learn on some of the important or critical questions on HBase which might be asked by the interviewer in an interview when you're applying for a big data admin or a developer position role. So what are the key components of HBase? Now, as I said, this is one of the favorite questions of interviewers, where they would want to understand your knowledge on different components for a particular service. HBase, as I said, is a NoSQL database, and that comes as a part of service with Cloudera or Hortonworks. And with Apache Hadoop, you could also set up HBase as an independent package. So what are the key components of HBase? HBase has a region server. Now, HBase follows the similar kind of topology like Hadoop. Now, Hadoop has a master process that is name node and slave processes such as data nodes and secondary name node. In the same way, HBase also has a master, which is HMaster, and the slave processes are called region servers. So these region servers are usually co-located with data nodes. However, it is not mandatory that if you have 100 data nodes, you would have 100 region servers. So it purely depends on admin. So what does this region server contain? So region server contains HBase tables that are divided horizontally into regions. Or you could say group of rows is called regions. So in HBase, you have 2 aspects. One is group of columns, which is called column family, and one is group of rows, which is called regions. Now these regions or these rows are grouped based on the key values, or I would say row keys, which are always unique. When you store your data in HBase, you would have data in the form of rows and columns. So group of rows are called regions, or you could say these are horizontal partitions of the table. So a region server manages these regions on the node where a data node is running. A region server can have up to 1,000 regions. It runs on every node and decides the size of region. So region server, as I said, is a slave process which is responsible for managing HBase data on the node. Each region server is a worker node or a worker process co-located with data node, which will take care of your read, write, update, delete request from the clients. Now, when we talk about more components of HBase, as I said, you have HMaster. So you would always have a connection coming in from a client or an application. What does HMaster do? It assigns regions. It monitors the region servers. It assigns regions to region servers for load balancing, and it cannot do that without the help of Zookeeper. So if we talk about components of HBase, there are three main components. You have Zookeeper, you have HMaster, and you have region server. Region server being the slave process, your HMaster being the master process, which takes care of all your table operations, assigning regions to the region servers, taking care of read and write requests which come from client. And for all of this, HMaster will take in help of Zookeeper, which is a centralized coordination service. So whenever a client wants to read or write or change the schema or any other metadata operations, it will contact HMaster. HMaster internally will contact Zookeeper. So you could have HBase set up also in high availability mode, where you could have a active HMaster and a backup HMaster. You would have a Zookeeper quorum, which is the way Zookeeper works. So Zookeeper is a centralized coordination service which will always run with a quorum of processes. So Zookeeper would always run with odd number of processes such as 3, 5, and 7. Because Zookeeper works on the concept of majority consensus. Now Zookeeper, which is a centralized coordination service, is keeping a track of all the servers which are alive, available, and also keeps a track of their status. For every server which Zookeeper is monitoring, Zookeeper keeps a session alive with that particular server. HMaster would always check with Zookeeper which region servers are available, alive, so that regions can be assigned to the region server. At one end, you have region server which are sending their status to the Zookeeper, indicating if they are ready for any kind of read or write operation. And at other end, HMaster is querying the Zookeeper to check the status. Now Zookeeper internally manages a meta table. Now that meta table will have information of which regions are residing on which region server and what row keys those regions contain. So in case of a read activity, HMaster will query Zookeeper to find out the region server which contains that meta table. Once HMaster gets the information of meta table, it can look into the meta table to find out the row keys and the corresponding region servers which contain the regions for those row keys. Now, if we would want to understand row key and column families in HBase, let's look at this, and it would be good if we could look this on an Excel sheet. So row key is always unique. It acts as a primary key for any HBase table. It allows logical grouping of cells and makes sure that all cells with the same row key are co-located on the same server. So as I said, you have 4 coordinates for HBase. You have a row key, which is always unique. You have column families, which is nothing but group of columns. And when I say column families, one column family can have any number of columns. So when I talk about HBase, HBase is 4-dimensional, and in terms of HBase, it is also called as a column-oriented database, which basically means that every row in one column could have a different data type. Now, you have a row key, which uniquely identifies the row. You have column families, which could be one or many, depending on how the table has been defined. And a column family can have any number of columns. Or I could say, for every row within a column family, you could have different number of columns. So I could say for my row 1, I could just have 2 columns such as name and city within the column family. For my row 2, I could have name, city, age, designation, salary. For my third row, I could have 1,000 columns, and all that could belong to one column family. So this is a horizontally scalable database. So column family consists of group of columns which is defined during table creation, and each column family can have any number of column qualifiers separated by a delimiter. Now, a combination of row key, column family, column qualifier such as name, city, age, and the value within the cell makes the HBase a unique 4-dimensional database. For more information, if you would want to learn on HBase, please refer this link, which is HBase Mapper, and this gives a complete HBase architecture, that is 3 components of name node, 3 components, that is name node, region servers, and Zookeeper, how it works, how HMaster interacts with Zookeeper, what Zookeeper does in coordination, how are the components working together, and how does HBase take care of read and write. Coming back and continuing, why do we need to disable a table? So there are different table operations what you can do in HBase, and one of them is disabling a table. Now if you would want to check the status of table, you could check that by is disabled and giving the table name, or is enabled and the table name. So the question is, why do we need to disable a table? Now if we would want to modify a table, or we are doing some kind of maintenance activity, in that case we can disable the table so that we can modify or change its settings. When a table is disabled, it cannot be accessed through the scan command. Now, if we have to write a code to open a connection in HBase, now to interact with HBase, one could either use a graphical user interface such as Hue, or you could be using the command line HBase shell, or you could be using HBase admin API if you are working with Java, or say HappyBase if you are working with Python, where you may want to open a connection with HBase so that you can work with HBase programmatically. In that case, we have to create a configuration object, that is configuration myconf, and then create a configuration object. And then you can use different classes like htable interface to work on a new table. You could use hcolumn qualifier and many other classes which are available in HBase admin API. What does replication mean in terms of HBase? So HBase, as I said, works in a cluster way. And when you talk about cluster, you could always set up a replication from one HBase cluster to other HBase cluster. So this replication feature in HBase provides a mechanism to copy data between clusters or sync the data between different clusters. This feature can be used as a disaster recovery solution that provides high availability for HBase. So if I have HBase cluster 1, where I have one master and multiple region servers running in a Hadoop cluster, I could use the same Hadoop cluster to create a HBase replica cluster, or I could have a totally different HBase replica cluster where my intention is that if things are changing in a particular table in cluster 1, I would want them to be replicated across different clusters. So I could alter the HBase table and set the replication scope to 1. Now a replication scope of 0 indicates that table is not replicated. But if we set the replication to 1, we basically will have to set up a HBase cluster where we can replicate HBase tables data from cluster 1 to cluster. So these are the commands which can be used to enable replication and then replicate the data of table across clusters. Can we import and export in HBase? Of course we can. It is possible to import and export tables from one HBase cluster to other HBase cluster, or even within a cluster. So we can use the HBase export utility, which comes in this particular package. Give a table name and then a target location. So that will export the data of a HBase table into a directory on HDFS. Then I could create a different table which would follow some kind of same definition as the table which was exported, and then I could use import to import the data from the directory on HDFS to my table. If you would want to learn more on HBase import and export, you could look at HBase import operations. Let's search for the link, and this is the link where you could learn more about HBase import export utilities, how you could do a bulk import, bulk export, which internally uses MapReduce, and then you could do a import and export into HBase tables. Moving further, what do we mean by compaction in HBase? Now, we all know that HBase is a NoSQL database which can be used to store huge amount of data. However, whenever a data is written in HBase, it is first written to what we call as write ahead log and also to memstore, which is write cache. Now, once the data is written in wall and your memstore, it is offloaded to form an internal HBase format file which is called H file. And usually these H files are very small in nature. So we also know that HDFS is good when we talk about few number of larger files in comparison to large number of smaller files due to the limitation of name nodes memory. Compaction is process of merging HBase files, that is these smaller H files, into a single large file. This is done to reduce the amount of memory required to store the files and number of disk seeks needed. So we could have a lot of H files which get created when the data is written to HBase, and these smaller files can then be compacted through a major or minor compaction, creating one big H file, which internally would then be written to HDFS and HDFS format of blocks. That is the benefit of compaction. There is also a feature called Bloom filter. So how does Bloom filter work? So Bloom filter or HBase Bloom filter is a mechanism to test whether a H file contains a specific row or a row column cell. Bloom filter is named after its creator, Burton Howard Bloom. It is a data structure which predicts whether a given element is a member of a set of data. It provides an in-memory index structure that reduces the disk reads and determines the probability of finding a row in a particular file. This is one of very useful features of HBase, which allows for faster access and avoids disk seeks. Does HBase have any concept of namespace? So namespace is when you have similar elements grouped together. So namespace, yes, HBase supports namespace. So namespace is a logical grouping of tables, analogous to a database in RDBMS. So you can create HBase namespace to the schema of RDBMS database. So you could create a namespace by saying create namespace and giving it a name. And then you could also list the tables within a namespace. You could create tables within a specific namespace. Now, this is usually done in production environment where a cluster might be multi-tenant cluster and there might be different users of the same NoSQL database. In that case, admin would create specific namespace, and for specific namespace, you would have different directories on HDFS, and users of a particular business unit or a team can work on their HBase objects within a specific namespace. This is a question which is again very important to understand about the writes or reads. So how does write ahead log wall help when a region server crashes? Now, as I said, when a write happens, it will happen into memstore and wall, that is your edit log or write ahead log. So whenever a write happens, it will happen in two places, memstore, which is the write cache, and wall, which is an edit log. Only when the data is written in both these places and based on the limitation of memstore, the data will be flushed to create an HBase format file called H file. These files are then compacted and created into one bigger file, which will then be stored on HDFS. And HDFS data, as we know, is stored in the form of blocks on the underlying data nodes. So if a region server hosting a memstore crashes, now where is region server running? That would be co-located with data node. So if a data node crashes, or if a region server which was hosting the memstore write cache crashes, data in memory, the data that in memory which was not persisted, is lost. Now, how does HBase recover from this? As I said, your data is written into wall and memstore at the same time. HBase recovers against that by writing to wall before the write completes. So whenever a write happens, it happens in memstore and wall at the same time. HBase cluster keeps a wall to record changes as they happen. and that's why we call it as also an edit log. If HBase goes down or the node that goes down, the data that was not flushed from memstore to H file can be recovered by replaying the write ahead log. And that's the benefit of your edit log or write ahead log. Now, if we would have to write HBase command to list the contents and update the column families of a table, I could just do a scan and that would give me complete data of a table. If you are very specific and if you would want to look at a particular row, then you could do a get table name and then give the row key. However, you could do a scan to get the complete data of a particular table. You could also do a describe to see what are the different column families. And if you would want to alter the table and add a new column family, it is very simple. You can just say alter, give the HBase table name, and then give your new column family name, which will then be added to the table. What are catalog tables in HBase? So as I mentioned, your Zookeeper knows the location of this internal catalog table, or what we call as the meta table. Now, catalog tables in HBase have two tables. One is HBase meta table and one is -root. The catalog table HBase meta exists as an HBase table and is filtered out of HBase shell's list command. So if I give a list command on HBase, it would list all the tables which HBase contains, but not the meta table. It's an internal table. This meta table keeps a list of all regions in the system and location of HBase meta stored in Zookeeper. So if somebody wants to find out or look for particular rows, they need to know the regions which contain that data, and those regions are located on region server. To get all this information, one has to look into this meta table. However, we will not be looking into meta table directly. We would just be giving a write or a read operation. Internally, your HBase master queries the Zookeeper. Zookeeper has the information of where the meta table exists, and that meta table which is existing on region server contains information of row keys and the region servers where those rows can be found. Your root table keeps a track of location of the meta table. What is hotspotting in HBase and how to avoid hotspotting? Now, this is a common problem, and always admin guys or guys who are managing the infrastructure would think about it. So one of the main idea is that HBase would be leveraging the benefit of HDFS. Your all read and write requests should be uniformly distributed across all of the regions in region servers. Otherwise, what's the benefit of having a distributed cluster? So you would have your data stored across region servers in the form of regions, which are horizontal partitions of the table. And whenever read and write requests happen, they should be uniformly distributed across all the regions in the region servers. Now, hotspotting occurs when a given region serviced by a region server receives most or all of read and write requests, which is basically a unbalanced way of read-write operations. Now, hotspot can be avoided by designing the row key in such a way that data being written should go to multiple regions across the cluster. So you could do techniques such as salting, hashing, reversing the key, and many other techniques which are employed by users of HBase. We need to just make sure that when the regions are distributed across region servers, they should be spread across region servers so that your read and write request can be satisfied from different region servers in parallel, rather than all read and write requests hitting the same region server, overloading the region server, which may also lead to the crashing of a particular region server. So these were some of the important questions of HBase, and then there are many more. Please refer to the link which I specified during my discussion, and that gives you a detailed explanation of how HBase works. You can also look into HBase Definitive Guide by O'Reilly or HBase in Action, and these are really good books to understand about HBase internals and how it works. Now that we have learned on Hive, which is a data warehousing package, we have learned on Pig, which is a scripting or a scripting language which allows you to do data analysis, and we have learned some questions on a NoSQL database. just note it that there are more than 225 NoSQL databases existing in market. And if you would want to learn and know about more NoSQL databases, you can just go to Google and type NoSQL databases.org, and that will take you to the link which is for NoSQL databases, and this shows there are more than 225 NoSQL databases existing in market, and these are for different use cases used by different users and with different features. So have a look at this link. Now, when you talk about data ingestion, so let's look at data ingestion, and this is one good link which I would suggest to have a look at, which lists down around 18 different ingestion tools. So when you talk about different data ingestion tools, some are for structured data, some are for streaming data, some are for data governance, some are for data ingestion and transformation, and so on. So have a look at this link, which also gives you a comparison of different data ingestion tools. So here, let's learn about some questions on Sqoop, which is one of the data ingestion tools mainly used for structured data, or you could say data which is coming in from RDBMS, or data which is already structured and you would want to ingest that. You would want to store that on HDFS, which could then be used for Hive, which could be used for any kind of processing using MapReduce or Hive or Pig or Spark or any other processing frameworks, or you would want to load that data into, say, Hive or HBase tables. Sqoop is mainly for structured data. It is extensively used when organizations are migrating from RDBMS to a big data platform, and they would be interested in ingesting the data, that is doing import and export of data from RDBMS to HDFS or vice versa. So let's learn about some important questions on Sqoop which you may be asked by an interviewer when you apply for a big data related position. How is Sqoop different from Flume? So this is a very common question which is asked. Sqoop, which is mainly for structured data. So Sqoop works with RDBMS. It also works with NoSQL databases to import and export data. So you can import data into HDFS. You can import data into data warehousing packets such as Hive directly, or also in HBase. And you could also export data from Hadoop ecosystem to your RDBMS. However, when it comes to Flume, Flume is more of a data ingestion tool which works with streaming data or unstructured data. So data which is constantly getting generated, for example, log files or metrics from server or some chat messenger and so on. So if you are interested in working on capturing and storing the streaming data in a storage layer such as HDFS or HBase, you could be using Flume. There could be other tools also like Kafka or Storm or Chukwa or Samza, NiFi, and so on. Sqoop, however, is mainly for structured data. Your loading data in Sqoop is not event driven, so it is not based on event. It basically works on data which is already stored in RDBMS. In terms of Flume, it is completely event driven. That is, as the messages or as the events happen, as the data is getting generated, you can have that data ingested using Flume. Sqoop works with structured data sources, and you have various Sqoop connectors which are used to fetch data from external data structures or RDBMS. So for every RDBMS such as MySQL, Oracle, DB2, Microsoft SQL Server, you have different connectors which are available. Flume, it works on fetching streaming data such as tweets or log files or server metrics from your different sources where the data is getting generated. And if you are interested in not only ingesting that data, which is getting generated in a streaming fashion, but if you would be interested in processing the data as it arrives, Sqoop can import data from RDBMS onto HDFS and also export it back to RDBMS. Flume is then used for streaming data. Now you could have one-to-one, one-to-many, or many-to-one kind of relation. So in terms of Flume, you have components such as your source, sink, and channel. That's the main difference between your Sqoop and Flume. What are the different file formats to import data using Sqoop? Well, there are lots and lots of formats in which you can import data into Sqoop. When you talk about Sqoop, you can have delimited text file format. Now that's the default import format. It can be specified explicitly using as text file argument. So when I want to import data from an RDBMS, I could get that data in HDFS using different compression schemes or in different formats using the specific arguments. So I could specify an argument which will write string-based representation of each record to output files with delimiters between individual columns and rows. So that is the default format which is used to import data using Sqoop. So to learn more about your Sqoop and different arguments which are available, you can click on sqoop.apache.org. You can look into the documentation, and I would suggest choosing one of the versions and looking into the user guide. And here you can search for arguments and look for specific control arguments which show how you can import data using Sqoop. So here we have common arguments, and then you also have import control arguments, wherein we have different options like getting data as avro, as sequence file, as text file, or Parquet file. These are different formats. You can also get data in default compression scheme, that is gzip, or you can specify compression codec, and then you can specify what compression mechanism you would want to use when you're importing your data using Sqoop. When it comes to default format for Flume, we could say sequence file, which is a binary format that stores individual records in record-specific data types. So these data types are manifested as Java classes, and Sqoop will automatically generate these data types for you. So Sqoop does that. When we talk about your sequence file format in terms of your Sqoop, you could be extracting storage of all data in binary representation. So as I mentioned, you can import data in different formats such as avro, Parquet, sequence file, that is binary format or machine readable format. And then you could also have data in different compression schemes. Let me just show you some quick examples here. So if I look in the content, and here I could search for a Sqoop based file where I have listed down some examples. So if I would want to use different compression schemes, here are some examples. Have a look at these. So I'm doing a Sqoop import. I'm also giving an argument so that Sqoop, which also triggers a MapReduce job, or I would say map only job. So when you run a Sqoop import, it triggers a map only job. No reduce happens here. And you could specify this parameter or this argument on the command line MapReduce.framework.name so that you could run your map only job in a local mode to save time, or that would interact with yarn and run a full-fledged map only job. We can give the connection and then connect to whatever RDBMS we are connecting, mentioning the database name, give your username and password, give the table name, give a target directory, or it would create a directory same as the table name, which would work only once. And then I could say -z to get data in a compressed format, that is gzip, or I could be specifying compression codec, and then I could specify what compression codec I would want to use, say snappy, bzip, lz4, default. I could also run a query by giving a Sqoop import. And when I'm specifying a query, if you notice, I've not given any table name because that would be included in the query. I can get my data as a sequence file format, which is a binary format, which will create a huge file. So we could also have compression enabled. And then I could say the output of my map job should use a compression at record level for my data coming in sequence file. So sequence file or a binary format supports compression at record level or at block level. I could get my data in an avro file where data has embedded schema within the file, or a Parquet file also. So these are different ways in which you can set up different compression schemes, or you can even get data in different formats, and you could be doing a simple Sqoop import for these. Looking further, what is the importance of eval tool in Sqoop? So there is something called as eval tool. So Sqoop eval tool allows users to execute user-defined queries against respective database servers and preview the result in the console. So either I could be running a straight away query to import the data into my HDFS, or I could just use Sqoop eval connect to my external RDBMS, specify my username and password, and then I could be giving in a query to see what would be the result of the query which we intend to import. Now, let's learn about how Sqoop imports and exports data between RDBMS and HDFS with its architecture. So RDBMS, as we know, has your database structures, your tables, which all of them are logical. And internally, there is always metadata which is stored. Your Sqoop import connects to an external RDBMS, and for this connection it uses an internal connector jar file which has a driver class. So that's something which needs to be set up by admin, but they need to make sure that whichever RDBMS you intend to connect to, they need to have the JDBC connector for that particular RDBMS stored within the Sqoop lib folder. So Sqoop import gets the metadata, and then for your Sqoop command, it converts that into a map only job, which might have one or multiple map tasks. Now that depends on your Sqoop command. You could be specifying that you would want to do a import only in one task or in multiple tasks. These multiple map tasks will then run on a section of data from RDBMS and then store it in HDFS. So at high level, we could say Sqoop will introspect database to gather the metadata. It divides the input data set into splits, and this division of data into splits mainly happens on primary key column of the table. Now, if somebody might ask, what if my table in RDBMS does not have a primary key column? Then when you're doing a Sqoop import, either you will have to import it using one mapper task by specifying -m equals 1, or you would have to say split by parameter to specify a numeric column from RDBMS. And that's how you can import the data. Let me just show you a quick example on this. So I could just look in again into the Sqoop command file, and here we could be looking at an example. So if you see this one, here we are specifying -m equals 1, which basically means I would want to import the data using one map task. Now in this case, whether the table has a primary key column or does not have a primary key column will not matter. But if I say a -MS6, where I'm specifying multiple map tasks to be imported, then this will look for a primary key column in the table which you are importing. Now, if the table does not have a primary key column, then I could be specifying a split by and then specify the column so that the data could be split into multiple chunks and multiple map tasks could take it. Now, if the second scenario is your table does not have a primary key column and it does not have a numeric column on which you could do a split by, in that case, and if you would want to use multiple mappers, you could still say split by on a textual column, but you will have to add this property so that it allows splitting the data which is non-numeric. All of these options are given in the sqoopapache.org link. Going further, how Sqoop imports and exports data between RDBMS and HDFS with its architecture. So as I said, it submits the map only job to the cluster, and then it basically does a import or export. So if we are exporting the data from HDFS, in that case, again, there would be a map only job. It would look at multiple splits of the data which is existing, which your map only job would process through one or multiple map task and then export it to RDBMS. Suppose you have a database test DB in MySQL. If somebody asked you to write a command to connect this database and import tables to Sqoop. So here is a quick example as I showed you in the command file. So you could say Sqoop import. This is what we would want to do. You connect using JDBC. Now this will only work if the JDBC connector already exists within your Sqoop lib directory. Admin has to set up that. So you can connect to your RDBMS. You can point to the database. So here our database name is test_db. I could give username, and then either I could give password on the command line or just say capital P so that I could be prompted for the password, and then I could give the table name which I would want to import. I could also be specifying -m and specify how many map tasks do I want to use for this import, as I showed in previous screen. How to export a table back to RDBMS? Now for this, we need the data in a directory on HDFS. So for example, there is a departments table in retail database, which is already imported into Sqoop, and you need to export this table back to RDBMS. So this is the content of the table. Now create a new department table in RDBMS. So I could create a table specifying the column names, whether that supports null or no, if that has a primary key column, which is always recommended. And then I can do a Sqoop export. I can connect to the RDBMS, specifying my username and password, specify the table into which you want to export the data, and then you give export directory pointing to a directory on HDFS which contains the data. This is how you can export data into table. Seeing example on this. So I could again look into my file, and here I have an example of import. This is where you are importing data directly into Hive, and you have Sqoop import where you are importing data directly into HBase table, and you can then query your HBase table to look at the data. You could also do a export by running your map only job in a local mode, connecting to the RDBMS, specifying your username, specifying the table where you would want to export, and the directory on HDFS where you have kept the relevant data. This is a simple example of export. Looking further, what is the role of JDBC driver in Sqoop setup? So as I said, if you would want to use Sqoop to connect to an external RDBMS, we need the JDBC ODBC connector jar file. Now, one or admin could download the JDBC connector jar file and then place the jar file within the Sqoop lib directory wherever Sqoop is installed. And this JDBC connector jar file contains a driver. Now, JDBC driver is a standard Java API which is used for accessing different databases in RDBMS. So this connector jar file is very much required, and this connector jar file has a driver class, and this driver class enables the connection between your RDBMS and your Hadoop structure. Each database vendor is responsible for writing their own implementation that will allow communication with the corresponding database, and we need to download the drivers which allow our Sqoop to connect to external RDBMS. So your JDBC driver alone is not enough to connect to Sqoop. We also need connectors to interact with different databases. So a connector is a pluggable piece that is used to fetch metadata and allow Sqoop to overcome the differences in SQL dialects. So this is how connection can be established. So normally your admins would, when they are setting up Sqoop and Hadoop, they would download, say, MySQL JDBC connector, and this is how they would go to the MySQL connectors. If you are connecting to MySQL, similarly for your other RDBMS, you could be, say, going in here, you could be looking for a previous version, depending, you could be going for platform independent, and then you could be downloading the connector jar file. Now, if you untar this jar file, you would see a MySQL connector jar. And if we look in com.mysql.jdbc.com.mysql.jdbc.driver. So this is the package which is within the connector jar file, and this has the driver class which allows the connection of your Sqoop with your RDBMS. So these things will have to be done by your admin so that you can have your Sqoop connecting to an external RDBMS. Now, how do you update the columns that are already exported? So if I do a export and I put my data in RDBMS, can I really update the columns that are already exported? Yes, I can, using a update key parameter. So Sqoop export command remains the same. The only thing I will have to specify now is the table name, your fields terminated by if you have a specific delimiter, and then you can say update key and then the column name. So this allows us to update the columns that are already exported in RDBMS. What is CodeGen? So Sqoop commands translate into your MapReduce job or map only job. So CodeGen is basically a tool in Sqoop that generates data access objects, DAO, Java classes that encapsulate and interpret imported records. So if I do a Sqoop CodeGen connect to an RDBMS using my username and give a table, this will generate a Java code for employee table in the test database. So this code gen can be useful for us to understand what data we have in this particular table. Finally, can Sqoop be used to convert data in different formats? I think I already answered that, right? If no, which tools can be used for this purpose? So Sqoop can be used to convert data in different formats, and that depends on the different arguments which you use when you do a import, such as Avro file, Parquet file, binary format with record or block level compression. So if you're interested in knowing more on different data formats, then I think I can suggest a link for that. And we can say Hadoop formats. I think it is Tech, Maggie, Avro, Parquet. Let's see if we can find out the link. Tech Maggie. Yeah, this is a very good link which specifies or talks about different data formats which you should know, such as your text file format, different compression schemes, how is data organization, what are the common formats, what do you have in text file, structured, binary, sequence files with compression, without compression, what is record level, what is block level, what is a Avro data file, what is a Sqoop, what is a Parquet data file or a columnar format, and other formats like ORC, RC, and so on.
Apache Spark is a popularly used analytics engine for big data processing. Hi everyone, welcome to this live session on Spark full course. In this session, you will learn the critical concepts in Spark starting from basics to advanced for handling data efficiently. You will learn the important components of Spark with hands-on demonstrations. Our experienced instructor Ajay will take us through this live session. But before we begin, make sure to subscribe to the Simplilearn channel and hit the bell icon to never miss an update. So we will start by understanding the basics of Apache Spark and look at how to install Spark on Windows and Ubuntu. Moving further, you will understand the Spark architecture in detail. Next, you will see the different components of Spark starting with Spark streaming. Then, you will learn how to query data using Spark SQL and perform machine learning operations with the help of Spark machine learning library. You will also focus on how to use PySpark to analyze Walmart stock data.
Welcome to this tutorial on Apache Spark, one of the most in-demand technologies and processing frameworks in the big data world. And here we will learn on Apache Spark, history of Spark, what is Spark, Hadoop, which is a framework again, Wes Spark, components of Apache Spark, that is Spark Core, Spark SQL, Spark Streaming, Spark MLlib, and graphics. Then we will learn on Spark architecture, applications of Spark, Spark use cases. So let's begin with understanding about history of Apache Spark. It all started in 2009 as a project at UC Berkeley AMP Labs by Mate Zaheria. In 2010, it was open sourced under a BSD license. In 2013, Spark became an Apache top-level project, and in 2014, used by Databricks to sort large-scale datasets, and it set a new world record. So that's how Apache Spark started. And today it is one of the most in-demand processing framework, or I would say in-memory computing framework, which is used across the big data industry. So what is Apache Spark? Let's learn about this. Apache Spark is an open source in-memory computing framework, or you could say data processing engine, which is used to process data in batch and also in real time across various cluster computers. And it has a very simple programming language behind the scenes, that is Scala, which is used. Although if users would want to work on Spark, they can work with Python, they can work with Scala, they can work with Java, and so on, even R for that matter. So it supports all these programming languages, and that's one of the reasons that it is called polyglot, wherein you have good set of libraries and support from all the programming languages. and developers and data scientists incorporate Spark into their applications or build Spark-based applications to process, analyze, query, and transform data at a very large scale. So these are key features of Apache Spark. Now, if you compare Hadoop with Spark, we know that Hadoop is a framework and it basically has MapReduce, which comes with Hadoop for processing data. However, processing data using MapReduce in Hadoop is quite slow because it is a batch-oriented operation and it is time-consuming. If you talk about Spark, Spark can process the same data 100 times faster than MapReduce, as it is a in-memory computing framework. Well, there can always be conflicting ideas saying, what if my Spark application is not really efficiently coded and my MapReduce application has been very efficiently coded? Well, then it's a different case. However, normally, if you talk about code which is efficiently written for MapReduce or for Spark-based processing, Spark will win the battle by doing almost 100 times faster than MapReduce. So as I mentioned, Hadoop performs batch processing, and that is one of the paradigms of MapReduce programming model, which involves mapping and reducing, and that's quite rigid. So it performs batch processing. The intermittent data is written to HDFS and read back from HDFS, and that makes Hadoop's MapReduce processing slower. In case of Spark, it can perform both batch and real-time processing. However, a lot of use cases are based on real-time processing. Take an example of Macy's, take an example of retail giant such as Walmart, and there are many use cases who would prefer to do real-time processing, or I would say near real-time processing. So when we say real-time or near real-time, it is about processing the data as it comes in, or you're talking about streaming kind of data. Now, Hadoop or Hadoop's MapReduce obviously was started to be written in Java. Now you could also write it in Scala or in Python. However, if you talk about MapReduce, it will have more lines of code since it is written in Java, and it will take more times to execute. You have to manage the dependencies, you have to do the right declarations, you have to create your mapper and reducer and driver classes. However, if you compare Spark, it has few lines of code as it is implemented in Scala, and Scala is a statically typed, dynamically inferred language. It's very, very concise, and the benefit is it has features from both functional programming and object-oriented language. And in case of Scala, whatever code is written, that is converted into bytecodes, and then it runs in the JVM. Now, Hadoop supports Kerberos authentication. There are different kind of authentication mechanisms. Kerberos is one of the well-known ones, and it can really get difficult to manage. Now, Spark supports authentication via a shared secret. It can also run on Yarn, leveraging the capability of Kerberos. So what are Spark features which really makes it unique or in-demand processing framework? When we talk about Spark features, one of the key features is fast processing. So Spark contains resilient distributed datasets. So RDDs are the building blocks for Spark, and we'll learn more about RDDs later. So Spark contains RDDs, which saves huge time taken in reading and writing operations. So it can be 100 times, or you can say 10 to 100 times faster than Hadoop. When we say in-memory computing, here I would like to make a note that there is a difference between caching and in-memory computing. Think about it. Caching is mainly to support read-ahead mechanism where you have your data preloaded so that it can benefit further queries. However, when we say in-memory computing, we are talking about lazy evaluation. We are talking about data being loaded into memory only and only when a specific kind of action is invoked. So data is stored in RAM. So here we can say RAM is not only used for processing, but it can also be used for storage. And we can again decide whether we would want that RAM to be used for persistence or just for computing. So it can access the data quickly and accelerate the speed of analytics. Now, Spark is quite flexible. It supports multiple languages, as I already mentioned, and it allows the developers to write applications in Java, Scala, R, or Python. It's quite fault tolerance. So Spark contains these RDDs, or you could say execution logic, or you could say temporary data sets, which initially do not have any data loaded, and the data will be loaded into RDDs only when execution is happening. So these can be fault tolerant, as these RDDs are distributed across multiple nodes. So failure of one worker node in the cluster will really not affect the RDDs, because that portion can be recomputed. So it ensures loss of data, it ensures that there is no data loss, and it is absolutely fault tolerant. It is for better analytics. So Spark has rich set of SQL queries, machine learning algorithms, complex analytics, all of this supported by various Spark components, which we will learn in coming slides. With all these functionalities, analytics can be performed better in terms of Spark. So these are some of the key features of Spark. However, there are many more features which are related to different components of Spark, and we will learn about them. So what are these components of Spark which I'm talking about? Spark Core. So this is the core component, which basically has RDDs, which has a core engine which takes care of your processing. Now you also have Spark SQL. So people who would be interested in working on structured data, or data which can be structurized, would want to prefer using Spark SQL. And Spark SQL internally has components or features like data frames and data sets, which can be used to process your structured data in a much faster way. You have Spark streaming. Now that's again an important component of Spark, which allows you to create your Spark streaming applications, which not only works on data which is being streamed in, or data which is constantly getting generated, but you could also transform the data. You could analyze or process the data as it comes in smaller chunks. You have Spark's MLlib. Now this is basically a set of libraries which allows developers or data scientists to build their machine learning algorithms so that they can do predictive analytics, or prescriptive, descriptive, preemptive analytics, or they could build their recommendation systems or bigger, smarter machine learning algorithms using these libraries. And then you have graphics. So think about organizations like LinkedIn or say Twitter, where you have data which naturally has a network kind of flow. So data which could be represented in the form of graphs. Now here, when I talk about graphs, I'm not talking about pie charts or bar charts, but I'm talking about network related data. That is data which can be networked together, which can have some kind of relationship. Think about Facebook, think about LinkedIn, where you have one person connected to other person, or one company connected to other company. So if we have our data which can be represented in the form of network graphs, then Spark has a component called GraphX, which allows you to do graph-based processing. So these are some of the components of Apache Spark: Spark Core, Spark SQL, Spark Streaming, Spark MLlib, and graphics. So to learn more about components of Spark, let's learn here about Spark Core. Now this is the base engine, and this is used for large-scale parallel and distributed data processing. So when you work with Spark, at least and the minimum you would work with is Spark Core, which has RDDs as the building blocks of your Spark. So it is responsible for your memory management, your fault recovery, scheduling, distributing, and monitoring jobs on a cluster, and interacting with storage systems. So here I would like to make a key point that Spark by itself does not have its own storage. It relies on storage. Now that storage could be your HDFS, that is Hadoop system. It could be a database like NoSQL database such as HBase, or it could be any other database, say RDBMS, from where you could connect your Spark and then fetch the data, extract the data, process it, analyze it. So let's learn a little bit about your RDDs, resilient distributed datasets. Now Spark Core, which is the base engine or the core engine, is embedded with the building blocks of Spark, which is nothing but your resilient distributed dataset. So as the name says, it is resilient. So it is existing for a shorter period of time. Distributed, so it is distributed across nodes, and it is a data set where the data will be loaded or where the data will be existing for processing. So it is immutable, fault tolerant, distributed collection of objects. So that's what your RDD is. And there are mainly two operations which can be performed on an RDD. Now, to take an example of this, say I want to process a particular file. Now here I could write a simple code in Scala, and that would basically mean something like this. So if I say val, which is to declare a variable, I would say val x, and then I could use what we call as Spark context, which is basically the most important entry point of your application. So then I could use a method of Spark context, for example, that is text file, and then I could point it to a particular file. So this is just a method of your Spark context, and Spark context is the entry point of your application. Now here I could just give a path in this method. So what does this step do? It does not do any evaluation. So when I say val x, I'm creating an immutable variable, and to that variable I'm assigning a file. Now what this step does is it actually creates a RDD, resilient distributed data set. So we can imagine this as a simple execution logic, a empty data set which is created in memory of your node. So if I would say I have multiple nodes in which my data is split and stored, imagining that your Spark is working with Hadoop. So I have Hadoop which is using say 2 nodes, and this is my distributed file system HDFS, which basically means my file is written to HDFS, and it also means that the file related blocks are stored in the underlying disk of these machines. So when I say val x equals sc.text file, that is using a method of Spark context. Now there are various other methods like whole text files, parallelize, and so on. This step will create an RDD. So you can imagine this as a logical data set which is created in memory across these nodes, because these nodes have the data. However, no data is loaded here. So this is the first RDD, and I can say first step in what we call as a DAG. A DAG which will have series of steps which will get executed at later stage. Now later I could do further processing on this. I could say val y, and then I could do something on x. So I could say x dot map, and I would want to apply a function to every record or every element in this file, and I could give a logic here, x.map. Now this second step is again creating an RDD, a resilient distributed data set. You can say second step in my DAG, okay, and here you have a external RDD, one more RDD created, which depends on the first RDD. So my first RDD becomes the base RDD or parent RDD, and the resultant RDD becomes the child RDD. Then we can go further, and we could say val z, and I would say, okay, now I would want to do some filter on y. So this filter which I am doing here, and then I could give a logic. Might be I'm searching for a word, I'm searching for some pattern. So I could say val z equals y.filter, which again creates one more RDD, a resilient distributed data set in memory. And you can say this is nothing but one more step in the DAG. So this is my DAG, which is a series of steps which will be executed. Now here, when does the execution happen? When will the data get loaded into these RDDs? So all of this, that is using a method, using a transformation like map, using a transformation like filter or flat map or anything else, these are your transformations. So the operations such as map, filter, join, union, and many others will only create RDDs, which basically means it is only creating execution logic. No data is evaluated, no operation is happening right now. Only and only when you invoke an action, that is, might be you want to print some result, might be you want to take some elements and see that, might be you want to do a count. So those are actions which will actually trigger the execution of this DAG right from the beginning. So if I here say z dot count, where I would want to just count the number of words which I'm filtering, this is an action which is invoked, and this will trigger the execution of DAG right from the beginning. So this is what happens in a Spark. Now, if I do a z.count again, it will start the whole execution of DAG again right from the beginning. So my z.count, second time an action is invoked, again the data will be loaded in the first RDD, then you will have map, then you will have filter, and finally you will have result. So this is the core concept of your RDDs, and this is how RDD works. So mainly in Spark, there are two kinds of operations. One is your transformations and one is your actions. Transformations or using a method of Spark context will always and always create an RDD, or you could say a step in the DAG. Actions are something which will invoke the execution, from the first RDD till the last RDD where you can get your result. So this is how your RDDs work. Now, when we talk about components of Spark, let's learn a little bit about Spark SQL. So Spark SQL is a component, a processing framework, which is used for structured and semi-structured data processing. So usually people might have their structured data stored in RDBMS or in files where data is structured with particular delimiters and has a pattern. And if one wants to process this structured data, if one wants to use Spark to do in-memory processing and work on this structured data, they would prefer to use Spark SQL. So you can work on different data formats, say CSV, JSON. You can even work on smarter formats like Avro, Parquet, even your binary files or sequence files. You could have your data coming in from an RDBMS, which can then be extracted using a JDBC connection. So at the bottom level, when you talk about Spark SQL, it has a data source API, which basically allows you to get the data in whichever format it is. Now, Spark SQL has something called as data frame API. So what are data frames? Data frames, in short, you can visualize or imagine as rows and columns, or if your data can be represented in the form of rows and columns with some column headings. So data frame API allows you to create data frames. So like my previous example, when you work on a file, when you want to process it, you would convert that into an RDD using a method of Spark context or by doing some transformations. So in the similar way, when you use data frames or when you want to use Spark SQL, you would use Spark's context, which is SQL context or Hive context or Spark, which allows you to work with data frames. So like in my earlier example, we were saying val x equals sc.text file. Now in case of data frames, instead of sc, you would be using, say, Spark dot something. So Spark context is available for your data frames API to be used. In older versions like Spark 1.6 and so on, we were using Hive context or SQL context. So if you were working with Spark 1.6, you would be saying val x equals SQL context dot. Here we would be using Spark dot. So data frame API basically allows you to create data frames out of your structured data, which also lets Spark know that data is already in a particular structure. It follows a format, and based on that, your Spark's backend DAG scheduler, right? So when I say about DAG, I talk about your sequence of steps. So Spark is already aware of what are the different steps involved in your application. So your data frame API basically allows you to create data frames out of your data. And data frames, when I say, I'm talking about rows and columns with some headings. And then you have your data frame DSL language, or you can use Spark SQL or Hive query language. Any of these options can be used to work with your data frames. So to learn more about data frames, follow in the next sessions. When you talk about Spark streaming, now this is very interesting for organizations who would want to work on streaming data. Imagine a store like Macy's, where they would want to have machine learning algorithms. Now, what would these machine learning algorithms do? Suppose you have a lot of customers walking in the store and they are searching for particular product or particular item. So there could be cameras placed in the store, and this is being already done. There are cameras placed in the store which will keep monitoring in which corner of the store there are more customers. Now, once camera captures this information can be streamed in to be processed by algorithms, and those algorithms will see which product or which series of product customers might be interested in. And if this algorithm in real time can process based on the number of customers, based on the available product in the store, it can come up with a attractive alternative price, so that which the price can be displayed on the screen and probably customers would buy the product. Now, this is a real-time processing where the data comes in, algorithms work on it, do some computation and give out some result, and which can then result in customers buying a particular product. So the whole essence of this machine learning and real-time processing will really hold good if and when customers are in the store. Or this could relate to even an online shopping portal where there might be machine learning algorithms which might be doing real-time processing based on the clicks which customer is doing. Based on the clicks, based on customer history, based on customer behavior, algorithms can come up with recommendation of products or better altered price so that the sale happens. Now, in this case, we would be seeing the essence of real-time processing only in a fixed or in a particular duration of time. And this also means that you should have something which can process the data as it comes in. So Spark Streaming is a lightweight API that allows developers to perform batch processing and also real-time streaming and processing of data. So it provides secure, reliable, fast processing of live data streams. So what happens here in Spark Streaming in brief? So you have an input data stream. Now that data stream could be a file which is constantly getting appended. It could be some kind of metrics. It could be some kind of events based on the clicks which customers are doing or based on the products which they are choosing in a store. This input data stream is then pushed in through a Spark Streaming application. Now, Spark Streaming application will break this content into smaller streams, what we call as discretized streams, or batches of smaller data on which processing can happen in frames. So you could say, process my file every 5 seconds for the latest data which has come in. Now, there are also some Windows-based options. Like when I say Windows, I mean a window of past 3 events. Window of past 3 events, each event being of 5 seconds. So your batches of smaller data is processed by Spark engine, and this processed data can then be stored or can be used for further processing. So that's what Spark Streaming does. When you talk about MLlib, it's a low-level machine learning library that is simple to use, scalable, and compatible with various programming languages. Now, Hadoop also has some libraries, like you have Apache Mahout, which can be used for machine learning algorithms. However, in terms of Spark, we are talking about machine learning algorithms which can be built using MLlib's libraries, and then Spark can be used for processing. So MLlib eases the deployment and development of scalable machine learning algorithms. I mean, think about your clustering techniques. So think about your classification, where you would want to classify the data, where you would want to do supervised or unsupervised learning. Think about collaborative filtering and many other data science related techniques or techniques which are required to build your recommendation engines or machine learning algorithms can be built using Spark's MLlib. GraphX is Spark's own graph computation engine. So this is mainly if you are interested in doing a graph-based processing. Think about Facebook, think about LinkedIn, where you can have your data which can be stored, and that data has some kind of network connections, or you could say it is well networked. I could say X is connected to Y, Y is connected to Z, Z is connected to A. So X, Y, Z, A, all of these are, in terms of graph terminologies, we call as vertices or vertex, which are basically being connected. And the connection between these are called edges. So I could say A is friend to B. So A and B are vertices, and friend a relation between them is the edge. Now, if I have my data which can be represented in the form of graphs, if I would want to do a processing in such way, this could be not only for social media, it could be for your network devices, it could be a cloud platform, it could be about different applications which are connected in a particular environment. So if you have data which can be represented in the form of graph, then GraphX can be used to do ETL, that is extraction, transformation, load, to do your data analysis, and also do interactive graph computation. So GraphX is quite powerful. Now, when you talk about Spark, your Spark can work with your different clustering technologies. So it can work with Apache Mesos. That's how Spark came in, where it was initially to prove the credibility of Apache Mesos. Spark can work with Yarn, which is usually you will see in different working environments. Spark can also work as standalone. That means without Hadoop, Spark can have its own setup with master and worker processes. So usually, or you can say technically, Spark uses a master-slave architecture. Now that consists of a driver program that can run on a master node. It can also run on a client node. It depends on how you have configured or what your application is. And then you have multiple executors which can run on worker nodes. So your master node has a driver program, and this driver program internally has the Spark context. So your Spark, every Spark application will have a driver program, and that driver program has a inbuilt or internally used Spark context, which is basically your entry point of application for any Spark functionality. So your driver or your driver program interacts with your cluster manager. Now, when I say interacts with cluster manager, so you have your Spark context, which is the entry point that takes your application request to the cluster manager. Now, as I said, your cluster manager could be, say, Apache Mesos, it could be Yarn, it could be Spark standalone master itself. So your cluster manager in terms of Yarn is your resource manager. So your Spark application internally runs as series or set of tasks and processes. Your driver program, wherever that is run, will have a Spark context, and Spark context will take care of your application execution. How does that do it? Spark context will talk to cluster manager. So your cluster manager could be Yarn, and in terms of when I say cluster manager for Yarn would be resource manager. So at high level, we can say a job is split into multiple tasks, and those tasks will be distributed over the slave nodes or worker nodes. So whenever you do some kind of transformation or you use a method of Spark context, an RDD is created, and this RDD is distributed across multiple nodes. As I explained earlier, worker nodes are the slaves that run different tasks. So this is how a Spark architecture looks like. Now we can learn more about Spark architecture and its interaction with Yarn. So usually what happens when your Spark context interacts with the cluster manager. So in terms of Yarn, I could say resource manager. Now we already know about Yarn. So you would have, say, node managers running on multiple machines, and each machine has some RAM and CPU cores allocated for your node manager. On the same machine, you have the data nodes running, which obviously are there to have the Hadoop related data. So whenever an application wants to process the data, your application via Spark context contacts the cluster managers, that is resource manager. Now what does resource manager do? Resource manager makes a request. So resource manager makes requests to the node manager of the machines wherever the relevant data resides, asking for containers. So your resource manager is negotiating or asking for containers from node manager, saying, hey, can I have a container of 1 GB RAM and 1 CPU core? Can I have a container of 1 GB RAM and 1 CPU core? And your node manager, based on the kind of processing it is doing, will approve or deny it. So node manager would say, fine, I can give you the container. And once this container is allocated or approved by node manager, resource manager will basically start an extra piece of code called app master. So app master is responsible for execution of your applications, whether those are Spark applications or MapReduce. So your application master, which is a piece of code, will run in one of the containers. That is, it will use the RAM and CPU core, and then it will use the other containers which were allocated by node manager to run the tasks. So it is within this container which can take care of execution. So what is a container? A combination of RAM and CPU core. So it is within this container we will have a executor process which would run, and this executor process is taking care of your application related tasks. So that's how overall Spark works in integration with Yarn. Now let's learn about this Spark cluster managers. As I said, Spark can work in a standalone mode, so that is without Hadoop. So by default, applications submitted to Spark standalone mode cluster will run in FIFO order, and each application will try to use all the available nodes. So you could have a Spark standalone cluster, which basically means you could have multiple nodes. On one of the nodes, you would have the master process running, and on the other nodes you would have the Spark worker processes running. So here we would not have any distributed file system because Spark is standalone and it will rely on an external storage to get the data, or probably the file system of the nodes where the data is stored, and processing will happen across the nodes where your worker processes are running. You could have Spark working with Apache Mesos. Now, as I said, Apache Mesos is an open source project to manage your computer clusters and can also run Hadoop applications. Apache Mesos was introduced earlier, and Spark came in and has existence to prove the credibility of Apache Mesos. You can have Spark working with Hadoop's Yarn. This is something which widely you will see in different working environments. So Yarn, which takes care of your processing and can take care of different processing frameworks, also supports Spark. You could have Kubernetes. Now that is something which is making a lot of news in today's world. It is an open source system for automating deployment, scaling, and management of containerized applications. So where you could have multiple Docker-based images which can be connecting to each other. So Spark also works with Kubernetes. Now let's look at some applications of Spark. So JP Morgan Chase and company uses Spark to detect fraudulent transactions, analyze the business spends of an individual to suggest offers, and identify patterns to decide how much to invest and where to invest. So this is one of the examples of banking. A lot of banking environments are using Spark due to its real-time processing capabilities and in-memory faster processing, where they could be working on fraud detection or credit analysis or pattern identification and many other use cases. Alibaba Group, that uses also Spark to analyze large data sets of data such as real-time transaction details. Now that might be based online or in the stores, looking at the browsing history in the form of Spark jobs, and then provides recommendations to its users. So Alibaba Group is using Spark in its e-commerce domain. You have IQVIA. Now, this is a leading healthcare company that uses Spark to analyze patients' data, identify possible health issues, and diagnose it based on their medical history. So there is a lot of work happening in healthcare industry where real-time processing is finding a lot of importance, and real-time and faster processing is what is required. So healthcare industry and IQVIA is also using Spark. You have Netflix, which is known, and you have Riot Games. So entertainment and gaming companies like Netflix and Riot Games use Apache Spark to showcase relevant advertisements to their users based on the videos that they have watched, shared, or liked. So these are few domains which find use cases of Spark, that is banking, e-commerce, healthcare, entertainment, and then there are many more which are using Spark in their day-to-day activities for real-time, in-memory, faster processing. Now, let's discuss about Spark's use case, and let's talk about Conviva, which is world's leading video streaming companies. So video streaming is a challenge. Now, if you talk about YouTube, which has data, you could always read about it. So YouTube has data which is worth watching 10 years. So there is huge amount of data where people are uploading their videos or companies are doing advertisements, and this videos are streamed in or can be watched by users. So video streaming is a challenge, and especially with increasing demand for high quality streaming experiences. Conviva collects data about video streaming quality to give their customers visibility into the end user experience they are delivering. Now, how do they do it? Apache Spark again. Using Apache Spark, Conviva delivers a better quality of service to its customers by removing the screen buffering and learning in detail about network conditions in real time. This information is then stored in the video player to manage live video traffic coming in from 4 billion video feeds every month to ensure maximum retention. Now, using Apache Spark, Conviva has created an auto diagnostics alert. It automatically detects anomalies along the video streaming pipeline and diagnoses the root cause of the issue. Now, this really makes it one of the leading video streaming companies based on auto diagnostic alerts. It reduces waiting time before the video starts. It avoids buffering and recovers the video from a technical error. And the whole goal is to maximize the viewer engagement. So this is Spark's use case, where Conviva is using Spark in different ways to stay ahead in video streaming related deliveries. So let's have a quick demo on setting up Spark on Windows and trying out the Spark's interactive way of working. For this, first thing is you will have to download Spark. Now you can just go to Google and type Spark download. And once you click on this link, it shows you a Spark release, a package type which says pre-built. So we will have to get a pre-built Apache Hadoop related Spark. So here I will choose say Spark 2.4.3 and I will choose pre-built for Apache 2.6, and then I can just click and download on this Spark 2.4.3 bin Hadoop 2.6 tar file. Once you click on this link, takes you to the mirror site, and you can just click on this link and download Spark 2.4.3. Once this is done, which I have already downloaded, here I can go to my downloads and it shows that I have a tar file. Now we will have to untar it or unzip it. So I can click on this link, and I already have WinZip, which allows me to unzip Spark 2.4.3. I can choose a location. So I can say unzip, click on unzip, choose local, and then I can choose one of my folders. So I have already unzipped it here. And that's how my Spark 2.4.4 directory exists here, 2.4.3, I'm sorry. Now let's go and look into this directory and what it contains. So I can click on C drive and then Spark 2.4.3, and this has the folders which are required for us to use Spark. If you look in bin, we have different applications and commands which we can use. And if you also see, I would have added one of the utilities here. Either we can have the Win utils, because Spark will need Hadoop and we are planning to use Spark on Windows. So what we need is this. So I have in my desktop a Hadoop directory which has a bin folder, and here I have downloaded a Win utils executable file, which you can always search on internet, and you can say download Win utils .exe for Spark 64-bit, and then you can find the link from where you can download this. For example, we can click on this, and here we can search for WinUtils. So here we have the link. I can open this link in a different tab, and this basically shows me WinUtils for Hadoop 2.7.1. Similarly, you can search for Hadoop 2.6 and you can download. However, 2.7 will also work fine. Now I have downloaded winutils.exe, and that's in this Hadoop folder. Within bin, I have this. So we need two things here. One is Spark, which is untarred and in a particular location, and then your Hadoop, which has bin, and this has WinUtils. Now, once you have these things, you can set your environment variables by just type in envir, go to your edit system environment variables, click on environment variables, and here if you see, I have added two variables. So you can just click on new and then you can give your variable name as Hadoop underscore home, and then you can give the path where you have your Hadoop directory that contains bin and that contains winutil.exe. I also have added Spark home, which points to my Spark directory. Now, once you have this, you are ready to use your Spark on Windows in local mode. Once this is done, I can open up my command prompt, and here I need to go to my Spark directory. I can just say cd spark 2.4.3, and then I can do a dir/p, which shows me the folders where we have bin. So to execute Spark, we can look into what our bin has, and it has different programs, such as you have Spark Shell to work with Scala and in an interactive way of working with Spark. You can also use PySpark, which allows you to use Python to work with Spark. And you also have Spark Submit if you have packaged your application in a jar file to submit it on a cluster. So in this case, we would be using Spark in a local mode. So let's use Spark Shell and test it. So I can just say Spark Shell in this way to start my Spark in an interactive way. Now, based on the path which you have set for your winutils.exe and Spark Shell, you should be able to use Spark. So it says, welcome to Spark version 2.4.3. It also shows that Spark context, which is the entry point of your application, is available as SC, wherein it is connecting to master as local and it has an application ID. It also shows you a Spark UI, which you can look at, and it says Spark session is available as Spark. So if you are interested in working with Spark core, that is with RDDs, we would be using Spark context. And if you are interested in working with Spark SQL, that is data frames and data sets, then we can be using Spark session. So let's try it out. So we can declare a variable that is an immutable variable. And now I will use Spark context with a method of Spark context. So I could just do a tab to see what are the available options within your Spark context. And here we can use one of them to read a file. So I will use sc.text file, and then I need to point to a file. So I already know that in my Spark directory, I have a file called readme.rd, and this is the method of Spark context. If I enter, it will create a RDD. Now, as I've explained about RDDs, these are resilient distributed datasets. There is no evaluation happening right now. So even if this file does not exist, I would still have an RDD created. Now I can go further and do some more transformations on this. So I could say val y, and then I could say take x. I would like to do a map transformation on it, and I would use to uppercase. Now this is a inbuilt function where I would want to convert the content of this file into uppercase. When I hit on enter, it again creates an RDD, and this RDD is basically a child RDD of the parent RDD created by text file. Remember, here we don't have any evaluation happening or any execution happening. It is just transformations which will lead to creation of further RDDs. Now we can invoke an action to see the result, and whenever you invoke an action, it will trigger the execution of your DAG starting from your first RDD till the last transformation you did before invoking an action. So I could just say count to see how many lines it has, and once I do this, it says input path does not exist. It is not able to find a file in this location. So this clearly explains that there was no evaluation happening when we did this, when we tried to read a file, and neither when we did a map transformation. Only and only when we invoked an action, it tried to search for file in this location. So let's quit this and check if the file exists. To quit, you can just do a Control D, or you could do a :quit. Now here, if you see some messages like this which says unable to delete temporary file, so that's a known issue. We can fix that, but my Spark is working fine. Now let's go and check if the file exists. So I will go in here, and then I will look in my Spark directory to see if the file exists. So this is the file readme.md. However, I had done readme.rd RD. So let's do it again and let's test if our Spark shell works fine. So we can go into the Spark directory by just doing this. And then either I could be going into bin directory and then start Spark shell, or some people prefer to do it this way, wherein you can say bin Spark shell, and that should start your Spark shell, but there was an error in the slash. So let's do it this way, and this will start your Spark shell, an interactive way of working with your Spark and using Spark context or Spark. Now once we have done this, I can again say val x, and I can say sc, which is Spark context, which is already initialized when you start your Spark shell. I can say text file, and I would want to read a file which is readme.md. Now we know that this file exists. However, the checking of the file existing or not, that means an evaluation, does not happen when you do a transformation or when you use a method of Spark context. It just creates an RDD. Click on this, and this has created an RDD of string. Now we can do further transformation on X by saying map, and then I can say I would want to convert the content into uppercase, and that's also done. Now finally, let's invoke an action which will trigger the execution of my tag which contains these RDDs. So I could just say Y, and I could say take 10, and I could say for each print ln, and this should be able to invoke an action, and it shows me the result from the file which is converted into uppercase. Remember, if I do a y.count, which is another action, it will trigger the execution of DAG right from the beginning where the first RTD was created. The transformation will be done, and then it will show me the count of lines which exist as a result of this. So we can do this, and this says me that there are 105 lines. This is a simple example of using Spark shell and using Spark in an interactive way on your Windows machine. Now to quit, we can always do a :quit, or we could do a Control D, and that basically takes you out of your Spark shell. Similarly, we can work on PySpark by just saying ./bin/PySpark, and that's Python's way of working with Spark, which brings your Python shell. It starts the Spark context, which is available as SC. And if you are interested in working on data frames or data sets using Spark SQL, then we would be using Spark. Now here, I can just declare a variable X, and I can just do sc.text file like what we did using Scala. We can be referring to the same file, readme.md, and this has created an RDD. You can just type in X, and that shows the RDD which was created. You can then further do some transformation on it using x.map, and then I could say I would want to convert this to uppercase. Now in case of Python, you would normally use lambda if you would want to do any kind of transformation. So I would say lambda x, and then I would want to convert this to uppercase. So here we can check if my RDD was correctly created, and as I was saying, we can then do some transformation on it. So I can say again y equals, and then I would want to do some transformation on X. I would say x.map. So in case of Python, as I explained, whenever we want to use an anonymous function or we want to do some transformation, then we can pass in the function to the transformation. So here I can say lambda, and then I can just say line, or I could say X or A, whatever that is, and I could say line. I would use an inbuilt function that is upper, which should convert the content of X to uppercase. Now remember, we are just doing some transformations here. So if I click on Y again and if I enter Y, it will show me that that has created an RDD. To see the content, I can just say y.collect, and that should show me the content of first few lines, which is converted in uppercase. So this clearly shows that we can even use Python to work with Spark by using PySpark. Now to quit this, we can just say quit, and that should take you out of your PySpark shell. So this is how you work on Spark Shell or PySpark on your Windows machine. So this has a local Spark setup, or basically Spark running in a local mode, and you could be using the interactive way of working with Spark. Now, if we have packaged our application in a jar file, then I could be using Spark Submit to submit my application. How do we do that? For this, we can basically bring up one of our IDEs. So in my case, I'm using Eclipse, and I can get into my Eclipse. Now there are two options here. One, we can be writing code in your IDE, that is Eclipse. We can be compiling the code based on the Spark related jars, and then we can run our application from IDE, which would interact with your Spark. That's one way. The second way is we can use packaging tools like SBT to package our application as jar and then push the jar to your local Spark or a Hadoop based Spark and then run it using Spark Submit. Now this is a simple sample application for which I have set up certain things here. The first thing is, when you have downloaded Eclipse, for all the people who are new, they might have to add the Scala plugin. Now if you see here in my Eclipse, it shows up Java perspective and it shows Scala perspective. Now how did I get this? You can click on help and you can say install new software, and here you can say add, you can say Scala IDE, and then you will have to give a link from where you can get the Scala IDE. How do I get that? So I can go to my browser and I can say scalaide.org, and once you go to this link, just scroll down, click on stable, and that shows you different releases for your different IDEs. Now for Eclipse, although this shows for Oxygen and I have Eclipse Neon, but that works fine. You can just copy this link, and here, once you have copied the link, give the location here, and you can say OK. Now once you do that, it shows you different options from where you can choose Scala IDE for Eclipse. Now in my case, it is already installed, so these options don't show up. However, if you do not have this option, for example, let's choose something else. Say I will say Scala search, and once I do this, next gets activated. So Scala IDE is already installed in my case, so I can click on next, and this should basically get Scala search plugin also, which can be added to my Eclipse. Now once this is done, you will be prompted to restart your Eclipse, and then you should have your Scala perspective. So for now, I'll just cancel this because I already have my Scala IDE.eclipse. So this is done. I'll just do a cancel here. Now once you have your Scala IDE or Scala plugin added to your IDE, you can always click on this icon here, and here you can just double click on Scala. That will open up Scala perspective. So that's the first thing. Then you can always click on File, New, and create a Scala project. For example, I could say My Test Apps, and then I can just say finish. So it has added a project. Now what we need to do is we need to make sure that our setup is fine. So first thing I would suggest is click on this, go to your build path, and here click on configure build path. So where it says Scala compiler, it would be good to choose for your project settings, instead of 2.12, go for 2.11. So sometimes you might have problems with Scala 2.12, which might not be able to compile for your Scala 2.11. So use latest 2.11 bundle, and then you can say apply. It says compiler settings have changed. A full rebuild is required for changes to take effect. Shall all projects be clean now? We can say OK, and we can say OK. So this will build your workspace to use Scala 2.11 bundle. Now once that is done, second thing what we need is we would want to write our code, and we would want our code to compile. For that, as I said, if we want to write our code using an IDE and then run it from our IDE rather than using a build tool like Maven or SBT, I can just add the Spark related jars to my build path. So I can right click here, I can say build path, and I can click on configure build path, and here where it says libraries, I can say add external jars. Now this needs my Spark related jars. Now where do I find it? So remember, we have downloaded Spark, so you can even find it there. So you can click on wherever your Spark is, and then you can click for jars, which shows you all Spark related jars. You can just do a Control A and just add it to your build path, say apply, and then just say OK. So once this is done, you have already added the Spark related jars, which might be good enough for you to write an application. Once this is done, we need to basically go ahead and write our code. Now, how do I do that? I can just click on source and I can say new, and then I can say package. And here you can say main.scala, click on finish, and that has created main.scala. So that would be source/main/scala in the folders. We can always check that. So I can go to C drive, I can look in users, Win10, and then look in my workspace for my project. And if you see in source, we have main and we have Scala. Now this is where we will be writing our code. So for this, then I can just right click and I can say new, and I can just create an object and I can give it a name. So we can say test app, and then we can say finish. So in case of Scala and Spark, we need to create an object and then we need to define main class here. Once that is done, we also need to import some packages and we need to initialize the Spark context. Now for that, you can take an example here. So I have already written the code and I can look in source, main Scala, and I have created an app called firstapp.scala. Now here we have the package name. We are importing some packages which are required for us to initialize Spark context and Spark configuration. So it is Spark context, Spark conf, and here is my object. And for a particular project, at least one of your object or one of your application needs to be the main. So we define the main here by saying def main args and array of string. Then we need to basically define our Spark context. So I'm creating a configuration object here, and then I say new Spark conf. I'm setting my application name to Hello Spark. And then this is very important. If you intend to run your Spark application either using Spark Submit or from your IDE, you need to specify your master as local. Now that could be given with one thread or multiple threads. So this is my configuration, and then I initialize my Spark context pointing to my configuration. So this is the most important part here. Now, if you see, this is something which I showed you in the command line. So I'm doing a val x and I'm pointing it to a file in my project directory, which is abc1.txt. So this is just to make sure that you are giving a Windows path and you're giving the right escape characters. Now, if you intend to run this application on a Hadoop based cluster, then you will have to give the path of the file accordingly, which we can see later. So here I have val x, I'm pointing it to a file which I have created here, and this just contains 3 lines. This is my sample file which I want to test. This is a new file. Now here I've created a variable called x. Further, I would say val y, and I would use Spark context method text file like what we did in an interactive way, and I'm pointing it to x. I'm also using some extra features like caching so that I can cache the RDD which gets created. Further, I create a variable called counts, and then I do a flat map transformation on y, where I would split the content based on space. I would do a map transformation where I would get every word from the file and map it with number 1. And finally, I do a reduce by key operation. Once this is done, I do a saves as text file. Now I could do a collect, I could do a take, I could do a count, and I could also do a save as text file where I would want my output to be saved in this location. Plus I'm using a Java utility to append a random number to my output directory. Finally, I do a Spark context stop. So this is my application, and if you see here, my application completely compiles because I've already added the relevant jar files in the build path. Now, once this application is done, we need to run this. But before doing that, we need to look into our run configurations. So you can click on run configurations, and here I'm giving my project name. I'm specifying my main class, which is first app. Then you can straight away go to environment, and here I have added two variables. One is Spark underscore local underscore IP, which points to this machine's local host. And then I've said Hadoop underscore home, because Spark, even when you're running locally, would want if Hadoop is existing. So we can just set Hadoop underscore home, and I'm pointing it to my desktop Hadoop directory, which contains bin folder, and that bin folder contains a winutils.exe. Once this is done, we are fine, and then I can test my application by just clicking on run. Now this should trigger my application on my Windows machine using my IDE. I didn't have to package this as jar, and here my application is completed, which should have created one additional directory here. So I can click on this, I can right click, and I can try doing a refresh. And here you see a new output is created. We can look into this. It has a part file which shows my word count. So this is a simple example of setting up your IDE and running your applications from IDE on a local Spark. Now what you also see is a build file here. What is that for? So in case you would want to create a project and you would want to package the application as a jar file and then run it on the cluster using Spark Submit. Now in that case, we can avoid adding the jars to my build path. But what I would need is I would need build.sbt file within my project folder. Remember, if you intend to package your application as a jar and then run it on a cluster or on a local setup, you would not need the build related jars. However, the build related jars which are already here will not cause any harm. Let them be there. Now we have a build.sbt file also, which is existing in my project folder. Now just for this run, I can in fact delete this target directory. It will be anyways recreated. And if you would want, we can also clean up these just to avoid the confusion. I will delete these. Now I just have my project folder and I have the libraries. I have abc1.txt and I have a build.sbt file. What does that contain? So this basically has a name. I'm giving a version which will be appended to my jar. I'm saying the Scala version which I'm using, which is 2.11.8, and I'm saying Spark version which is 2.2.0. You can replace these with the version which you intend to use. Other than that, we are pointing to the different Spark components and the relevant dependency related jars which your SBT can get for you. So I've given Spark Core, Spark SQL, MLlib, Spark Streaming, and Spark Hive, which will be then fetched from the repository. So this is my build.sbt file, which exists in my project folder. We have our code written. We have our build.sbt file, which is already existing in my project folder. My code is already fine. Now we need to use SBT to package my applications into jar, for which you will have to download SBT. So you can just say download SBT Windows, and that should take you to the installing SBT on Windows page. Now here you can just download the MSI installer and run through the installer, which will basically install SBT on your machine. Now I have already done that. So my build file is ready, my code is ready. All I need to do is now use SBT. So what I can do is from my command line, I can just say cd and I will go into users. I'll go into Win10 and I'll go into my workspace. Now here I can see for my projects and I can go into my Spark apps. Now, once I'm in my project folder, we can double check that it has a build.sbt, which is fine. SBT is already installed on this machine. And I can just say SBT. If you would want to check, you can always do SBT version to check if you have SBT. And this command is also done once you install SBT for the first time. You can always do SBT version, and before displaying SBT's version, it will try to fix all your dependencies. It will try to get all the relevant dependencies. So this is just to check that SBT is installed on my machine. As I said, my code is already ready. I have a build.sbt file and I can just say sbt package, which then will refer to build.sbt, will look for your code in source main Scala, and then if everything is fine, it will package it as jar and it will create folders within your project folder. We can click on this. We can try doing a refresh to see. Now, if you see here, the project was again created. A target folder is created. Within Scala 2.11, I will have my jar created. So we can see that my SBT was fine. It has packaged the code and it has created a jar file as simple project 2.11-1, which can be used to run on the cluster or in a local mode. Let's check in Eclipse. I'll click on this and I'll just do a refresh and I see my jar is already existing, which basically means then we can do a Spark submit. So this is where we see that I am already running a Spark submit command. Now this might show up some error messages, but we can see how we did this. So if you see here, once my packaging was done, I went into my Spark folder. I did a bin/Spark submit. I mentioned my jar file and then I said my class main.scala.firstApp. So this is my app and this is how I'm using Spark submit to submit an application which is running in local mode. So we can see further if it starts processing. So here it says created local directory. Then it starts an executor on local host. It goes for execution and then if we see further, we could also see it will add our jar to the class path and then finally it should be doing the execution. Now, if there is any error message that might be related to your file not being deleted or if there is any problem with executor, so we can basically come back and check here if there was any specific error. So the error was that it tries to delete a temp directory, but it does not have the permissions. So we have not done that. But as per my application, it should be creating a output in this folder as Spark out. So let's click on this and see. I'll do a refresh, right? And if you see, a new Spark output has been created. So in previous sessions, we have seen how we can set up Spark on Windows or set up our Spark related IDE so that we can run our applications on Windows. Now here we have a quick demo on setting up Spark as a standalone cluster on Ubuntu machines and then trying out Spark way of working, for which we need at least 2 machines. And here I have Ubuntu machines set up, UM1 and UM2, just to give insights on how my machines look. So if I look in my etc hosts, I have the IP address of multiple machines. So I can ping one machine to other machine by just doing a ping UM2 and that should work fine. Similarly, I have also set up SSH access for these machines. Both of the machines have HDU as the user and I can just do a SSH UM2 and that logs me into the second machine without a password. Similarly, I can check the same thing from my second machine by doing a SSH UM1 and that works fine too. So we need 2 machines which can ping each other, firewall disabled, able to SSH each other so that we can set up a standalone cluster of Spark. How do we do it? So first thing is we will have to download the Spark related tar file. Now I can just go to Google and I can type in Spark 2.2.1 download. Now that's what I'm interested in. And this takes you to Spark release 2.2.1. However, here it shows you the latest release is 2.4 and then 2.4.2. So what we can do is we can go to archives. So I can basically look at existing versions. Now here I can click on download and this shows me a Spark release and also pre-built for Apache Hadoop. Now what we can also do is we can go to release archives for an older stable version. I click on this, and here I have Spark 2.2.1. Now I can click on this and we can either install something which is not already built, or we can download this one, which is Spark 2.2.1 bin Hadoop 2.6.tgz. So you click on this link and then save this file, which I have already done. And here, if you see in my machine, I have home HDU downloads, which has my different packages which I've downloaded. Also, if you notice, I have downloaded JDK 8, so you can check on my machines. So apart from machines being able to ping each other and being able to do a SMI user local location. If you see here, this is the directory which is created, but you also see that there is a Spark link which is pointing to Spark. Now that is because if you would want to work on a newer version of Spark, you could just do the same thing for newer version and then make your link pointing to the newer version of Spark. How do you create a link? You can just say sudo ln -s, you can give your Spark directory, and then you can create a link. So I've already created a link, and my Spark path will then become this. Now what do we do with this? Once we have done this, once we have created a link, we can go into the bash file of my user. And if you carefully see here, I have given my Java path so that I can execute Java related commands. And I have also added my Spark related path here, which says user local Spark. So in case you would be changing your Spark version to a latest one, you will not have to change things in your bash file. Only thing you will have to do is unlink the existing Spark link and create a new link to your newer version. So this is done on this machine, and now I can basically be using Spark. Now before doing that, we can go into user local Spark, and this has different directories. So if you look in bin, these has the binaries programs like your PySpark, your Spark Shell, Spark SQL, and Spark Submit, which we will see how we can use here. If you look in sbin, it has other startup scripts to start your history server or to start your master or worker processes. If you look in conf, this has your config directories. Now here by default, you might see spark -default.conf.template. I have renamed that to .conf. Slaves template has been renamed to slaves. So let's look into this. So I can go into conf, and then I will look in spark default conf. Now here, based on our setup, now here we intend to set up a Spark standalone cluster that is without Hadoop, but I would want to have a Spark standalone distributed cluster. So I have uncommented this property which says spark.master, and I say Spark, and I also mentioned that my master will run on this machine, which is UM1. Spark event log .enabled is true because we would want to track the events. I have mentioned a directory. So this is a local directory in user local Spark, and we will have to create it. It talks about the default serializer. It talks about the driver memory, which was by default 5 GB. I have reduced it to 2 GB based on my machine configuration. You have Java options. And then if you intend to run a history server so that whenever your Spark applications complete, you will have your application stored in history server, I have given the log directory, which is user local Spark, and then application history, and this also needs to be created. We have Spark history provider for the class, which takes care of history server, and the update interval of looking for your applications. So this is what we have in our Spark default. And if you look in slaves, I have given the machines where I would want my worker processes to run. So that is UM1 and UM2. Now, once you have made your changes in your Spark default conf and slaves file, what you can simply do is SCP, assuming that whatever was done on this machine, that is untarring your Spark directory, creating a link, updating your bash RC, and renaming your config files. Same steps need to be done on the second machine, and your second machine would also be prepared to be used for your Spark cluster. So once you have both the machines which can ping each other, which can SSH each other, both of the machines have Java, both of the machines have the same Spark version downloaded and the basic setup done, I can just easily copy the Spark related config from here into my other machine, that is SDU UM2, and then I can give a path which is user local spark conf, and in this way I don't need to edit my config files again, and similarly I can even copy the slaves file. This is all we need to basically have our Spark standalone cluster. Now, since we have updated our bash RC, we can give our Spark command from anywhere. We have set up our config files, so I can just do a start -all.sh, and that based on my config files, based on the directories which are mentioned, it will start my master process and my worker process on both the machines. So here we have a Spark standalone cluster which has 2 workers and 1 master. Now we can always go to the browser interface and we can check for the Spark UI, which should be available by typing in http:// my master, and then the port is 8080. So this shows that I have a Spark master running. I have 2 worker processes. Right now there are no applications which are running, but my Spark UI is already available. When we start using Spark, either by Spark Shell or PySpark or even Spark Submit, we will see our applications getting populated here. Additionally, we can also start the start history server by just saying start history server.sh, and that will start my history server. Once this is done, we have a history server also running, and we can go back and then we can again pull out the history server user interface by giving in the port which is default 18080. So I have a Spark standalone cluster with 1 master, 2 workers, and also a history server which is running. Once we have this, we can try working with Spark, either with Spark Shell or PySpark, or if you have packaged your application as a jar using SBT or Maven, you could also use Spark Submit. Additionally, you could also use Spark SQL. So to work with Spark, I would just say Spark Shell on one of my machines. Both my machines which have worker processes running, we can start our Spark Shell on any of these machines. Remember, here our Spark will rely on the storage of these machines, that is the file system, because it does not have any Hadoop or distributed file system. We have started our Spark Shell, and that shows Spark Context, which is available as SC. Spark Session is available as Spark. So to work with Spark Core and RDDs, we would be using Spark Context, and if you intend to work with Spark SQL, that is data frames and data sets, you can be using Spark. Let's try a quick simple example. So I'll say val x sc.text file, and now I would want to point it to a file. So I will say the complete path. Remember, I'm giving the Spark command from my home directory. So I will have to say user local spark, and then I can point to a file which is existing here. And this is what I would want to use to do some processing. We are using the first step here, wherein we are using a method of Spark Context which will not relate in any evaluation, and it will just create an RDD. Now we are using the Scala's way, so let's create one more variable, and then we can do some transformation on it by saying to uppercase. I would just want to convert the content into uppercase, and this is again a transformation, so that will just create an RDD. Once this is done, we can invoke an action to basically see some results. So I could just simply do a collect, which is an action, and this action will trigger the execution of DAG, which starts from the farthest RDD. That is the first step where your file is loaded into RDD. Now once we do this, we should be able to see our result, and that basically is execution of DAG. So from the time we have used a text file, which is a method of Spark Context, to we did a transformation, and till we invoked an action becomes my one job. Now if I would do y.count, which is again a different action, this will trigger the execution of DAG right from the beginning. That is sc.txt file where the data will again be loaded in RDD. A map transformation will happen, and then you will have a count. Now we can always see this in the Spark UI by just going in here and just doing a refresh. So that will show me that there is an application which is running via Spark shell. It has utilized 3 cores. It has utilized memory per executor 1 GB, and we can click on this application, which shows that it used both the workers, 1 core and 1 GB on this worker, and 2 cores and memory on this worker. I can click on application detail UI, wherein I can see what are the actions I invoked. We also see the number of tasks which are run, and that is because every RDD which is created by default is having 2 partitions. And for each partition, you would have 1 task. Well, we can change the partitions and many more things can be done, but that you can learn in later sessions. Here we have 2 jobs. One ended with collect and one ended with count. Now I can click on collect, and I can see the DAG visualization, which tells me we started with a text file, we did a map, and finally we did a collect. It shows that everything was done in stage 0. That is just one stage. I can click on count, and that again shows me the DAG visualization, which is a different stage, a different job ID, which started with text file, map, and then we did a count. If you would want to see more details, you can always use these tabs to look at different stages within your application. If you were doing some caching, looking at environment variables, and also to see how many executors were used, including the one for the driver, on which nodes these executor ran, how many cores, how many tasks were run, was there any shuffling involved, and so on. So this is how I have used Spark Shell. That is an interactive way of running my application. And since we have a Spark UI, we can always look at applications when they have run, and we can always drill down and know more details. Now, since my application is completed, I can do a refresh on history server, but that does not show anything because when we started a Spark shell, it started an application, and that application is still in running status. If you see here under running applications. So this is how we use Spark shell on a standalone Spark cluster. Now we can just do a :quit, and that takes me out of Spark shell. Similarly, if I would want to work on PySpark, that is Python's way of working with Spark, I can just type in PySpark, which should bring my Python shell, and then I can continue working with Spark and again go back and look at my UI. While my PySpark comes up, I can go here. Since I quit my Spark shell, I can just do a refresh to see if my application is yet coming up in history server. It might take some time, and you can always go back and look at incomplete applications or wait till your application is populated in history server. Now, if I do a refresh here on Spark UI, it says this application was completed. It says finished. And then now we have started PySpark. So it has started a new application, PySpark shell, and that is in running status. We can come back here, and now we have our Python's way. So I can do the same thing which I did in Scala using sc.txt file. I will point it to a file which exists in user local spark readme.md. So that's the file which I'm interested in. Now this would have created an RDD, which we can confirm by just typing in X. Now I can create a different variable, and I can say I would want to do a transformation of map. Now in case of Python, when you use anonymous functions or when you want to apply some functions to your transformations, you use lambda functions. So we say lambda line, and then I would say what I want to do to the line. I will say I will use a inbuilt uppercase upper function, which should convert my content into uppercase. But as of now, this is a transformation, so it only creates an RDD. To see the result, I can do a y.collect, and that should bring up my result. Now, in case if it says the file does not exist, that is because there was a typo here, and we can repeat this step. So let's bring up here again X, and I can give the right name of the file. I can do a transformation, and finally I can see the result. So this is using PySpark on a standalone Spark cluster, which is working without Hadoop, which has 2 worker nodes and 1 master node. We can always come and do a refresh here to look at more details. So we have our application. We can click on this. Again, similarly, like we did for Scala application detail UI, I see my application ended at collect. It ran 2 tasks and I can look at my DAG. So this is how we can use Spark shell or PySpark. Let's spend some time in understanding the Spark's architecture. Now, when you talk about Spark architecture, it is based on 2 important abstractions. You have RDDs, which are the building blocks, that is resilient distributed data sets, which are the fundamental units of data, which are lazily in nature, or you can say implicitly lazy in nature. And these are created, as I explained earlier, whenever you use a method of Spark context or whenever you do a transformation on an existing RDD or a dataset. By default, every RDD has 2 partitions, which can then be customized while creating RDDs. So I could specify, if I know that my RDD would be based on a bigger file, I could break my RDD into several partitions. And how does that help? The more number of partitions you have, better will be your parallel processing. So your RDDs are automatically split into partitions, and then these can be executed upon on different nodes by different tasks in parallel in memory. You have the concept of DAG, which I explained earlier, that is directed acyclic graph. So basically Spark has a DAG scheduler in the backend, which is tracking the transformations or steps which you have as a part of your application. So DAG is basically a scheduling layer of Spark architecture. It implements stage-oriented scheduling and eliminates Hadoop's MapReduce multi-stage kind of execution model. The summary of this is that if you are processing data using Spark applications in a Spark platform, whether that is standalone or Hadoop cluster, for every step you do as a part of your application, it creates an RDD which becomes a part of your DAG. Now DAG scheduler is already aware of what are the steps involved in DAG, and it comes up with an execution plan to execute the DAG, to execute all the steps within a DAG, if and only if an action is invoked. So every Spark application has a driver program. Now Spark also works in master-slave architecture. It basically can have a master process and worker processes running across multiple machines. Your Spark could be interacting with cluster managers such as Apache Mesos or Yarn, where you would not have Spark's master or worker processes running. However, Spark would depend on the cluster manager, the cluster's master, and cluster's save for data processing. Every application has a driver program. Now that's a mandate, and every driver program has the entry point of your application, that is your Spark context. So Spark context is the one which takes your application request to the cluster manager, and then cluster manager takes it from there. So cluster manager, so in case if your Spark is working with Yarn, in that case, cluster manager would be resource manager, which would be negotiating resources to the node managers. Node managers which are running on the slave machines wherever your data nodes are running will approve or reject the resource request from resource manager. If approved, your node managers would be granting in containers. And what is a container? A combination of RAM and CPU cores. So once containers are allocated by your worker nodes or your node managers, your cluster manager, that is resource manager, starts application master that will run in one of the containers and use other containers to run the executor process, which will take care of different tasks on different partitions within a particular cluster. If we look further, this is how it looks. So executor is a JVM process. It runs within the container. It is responsible for execution of tasks, or I could say working upon tasks on a partition of RDD that exists respectively on that particular node. When we look further in Spark architecture, your worker nodes are the ones which are executing the tasks assigned by cluster manager and return the result back to Spark context. So always remember, your executor, which is responsible for execution of tasks, runs within the container, that is within a specific amount of RAM and CPU core, and we could have any number of executors running on a particular node in any number of containers. However, if a user runs an application asking for executor with specific amount of memory, specific amount of CPU cores, that is possible. However, the request should not exceed the container size. Finally, if we have understood and learned about your Spark components, your Spark architecture, we can also see running a Spark application. Now, a Spark application can run in a standalone mode. That is, you could set up your IDE such as Eclipse with a Scala plugin, and then you could have your coded application which is written in Eclipse to be run in local mode. Now here I have an example of application which can be run in a local mode or on a cluster. So this application is importing some packages, that is Spark Context, Spark Conf. I have created an object which is first app. It is the main class of your project, and other classes can just be extending app rather than having main. Here we declare a variable called x, which is pointing to a file in my project directory. It looks for a file which is abc1.txt, and this file basically has some content. What are we doing in the application? So we create a variable where we assign the file. Then we define or initialize our Spark context. So remember, whenever you work with IDE, you don't have Spark context or Spark available implicitly. That has to be defined. So here we create a configuration object. We set our application name. We set the master as local if you want to run it in a local mode. If you want to run it, say, on your Windows machine, or if you would want to run on a Spark standalone cluster. If I would be running it on Yarn, then I would remove this property that is set master. Now, once you have defined your configuration object, you can be basically using Spark context. You can use method of it, which will result in RDD. That is what is happening in line 13, val y. And then finally, I can create a variable where I would want to do a flat map transformation on y, which would result in an internal RDD, followed by a map transformation, which would again result in an RDD, and finally reduce by key, which is doing an aggregation. Once all these steps are done, I can decide to display the result on the screen, or I can even use save as text file, point it to a particular location, and then have my application run. Now, this is my Eclipse. Refer to other sessions where I've explained how you can set up IDE on Windows with different environment variables, and then you can run your applications on a particular cluster. If I would want to run this application on a cluster, then I will have to give a particular path. So here in this case, I can say, let's do this, and I will say my file is abc1.txt. Let's save it, and I'll also say my output will be getting stored in a default location. As I intend to run it, I intend to run this application on a cluster. Now in that case, the cluster would usually be set up on Linux machines, would have a Hadoop cluster where you can run this application. So if I would want to run this application on a cluster but not locally on the machine, I can just delete this part. I can keep my application. Now if you see, my application already compiles and does not show any error message, and that is because in my project's build path, I have added all the Spark related jars. All the Spark related jars you can get from your Spark directory, or you can be getting in manually all the dependencies. Some people would prefer to use Maven or say SBT for packaging your application as jar, and that can also be done. So here my code compiles, code is fine, it is pointing to a file, and then it is also creating an output which will have word count. Now what I can do is, since I have my code already written, I know that I have SBT installed on this machine because I would want to package this code as jar and run it on a cluster. So for that, we can look in our command prompt, and here I can go into workspace. I can go into my Scala project, and if you see here, we have your build.sbt file, you have your binaries, and you have your source. So you might not have these Spark related directories. Now these exist in my case because I have been using Spark and I've done some previous runs. Now this is what we have within my Spark apps. So to build my package, I need a build.sbt file. We can see what does that contain. So your build.sbt contains your name, version of your package jar, Scala version, Spark version, and then repository which Spark will refer to when it wants to have the dependencies for all of your components such as Spark Core, Spark SQL, MLlib, and so on. So this is my build.sbt file which exists in the project folder. And if you are intending to use SBT to package your code as jar and then run it on the cluster, in that case, I can even skip adding Spark related jars to the build path. So that is only done to make sure that your code compiles. Now, once I have my code written, I have SBT installed, I have made the file path changes, I can just go to the command line within my project folder and I can say SBT package. Now this will basically resolve all the dependencies based on whatever you have given in the code. It will create a jar file and place it in a particular location, and then we can use the same jar file to run on a particular cluster. So SBT package is busy in creating the jar. Now meanwhile what I can do is I can open up a lab content, and what I can do is I can just say, for example, Simplilearn. And here I already have a lab set up, so you could have your own Spark standalone cluster where you could also run this jar file. You could have Spark with Hadoop, which is what I have here, and I will use that to submit an application on the Yarn cluster. And let's go to the web console. Let me copy my link. I'll close this. I'll say launch lab, and then I can log in here. I can just do paste my password and I'm logged in. So I can just say Spark 2 shell. Now that's how it has been configured here to work with your Spark version 2. So this is an interactive way of bringing your Spark shell and running your application. But what we are interested in is running the application as a jar file. So let's go and see here where we have our code, and let's see if SBT has done the packaging. Yes, it has done, and it has created a jar file in this location. So what I can do is I need to get this jar file from this location onto my cluster. So what I can do is I can come in here, I can do a FTP. So this basically allows me to push whatever jars I have on my web console. So I'll go in here, I'll say connect. Now I'll search if there is already existing jar file which might create a conflict. So I have something here. So I can for now just delete it. It's done. I will say upload file, and I'm interested in getting the jar file. So here we can click on users, Win10. I have my workspace project. I can get into target, Scala 2.11, and take my jar file and say open. So this will upload my jar file on the web console or the terminal, wherein I can connect to my cluster. Now let's go in here. Let's quit from Spark Shell as we want to run an application on the cluster. How do I do it? So I can search if I have my jar file existing. It's here. So I'll say Spark to submit, and then I will point to my jar file, and then I can simply say class, and I know my code has a package and a class name. So this is package and this is my object or class name. So I can say main.scala.first_app. Now it will be good if we check if the file exists, which our code points to. So I'll just for now comment it out. I will check in my HDFS ls in my default user directory. This is where it will search for a file, and here we can search if I have a file called ABC. So I don't see anything here. So let's do this. What I can do is I can again go to FTP, and basically I can do a upload file like what we did earlier, and this time I'll pick up this existing ABC1 file which I showed you and upload it. Once this is done, I can put it on my cluster by just saying HDFS, DFS, put, let's take the ABC1 file and let's put it in my directory. So this will be my input. So I'm putting in a file there, and now I can do a Spark submit to submit the application on the cluster. So if you see here, it has basically started the application. It contacts the resource manager. It gets an application ID, and now it is doing the processing of my file where I would want to get. Once this is done, it will be completed and the temporary directory will be deleted. So this is how I run a Spark application on a cluster. Now, once this is done, I can also go to Spark's history server by saying, this is the path for my Spark history server. It shows an application which was run today, which was doing a word count. You can click on the application. It says it ended with save as text file. You can click on this, and then it shows you the DAG visualization. It says we started with text file. We did a flat map, we did a map, and then there was some shuffling because we wanted to do reduce by key. So as I said, every RDD by default has two partitions. And if you want to do some aggregate or wider transformations like reduce by key, sort by key, group by key, count by key, and so on, in that case, similar key related data has to be shuffled and brought into one partition. That's where we see shuffling happening here, and it also tells what are the number of tasks which have run per partition. So here we ran a Spark application by packaging it as jar using your SBT. So SBT created the jar file, and then basically we brought our jar file onto the cluster and then submitted it using Spark submit. So this is how a Spark application runs on the cluster. So as I said, your application has a driver program. Now your Spark applications run as independent processes, and they can run on a cluster across the nodes. So we just saw how we can run a Spark application on a cluster. Now we can always look at Spark application's progress or after it has completed by looking into the Spark UI. Your Spark application, as I mentioned, has a driver program, and when you run your application on the cluster, you can always specify where would you want your driver program to run. So in our case, when we ran our Spark application here, we basically just did a simple Spark submit, and we gave our jar and the class name. I could also say master, and then I could specify if I would want my application to run in a local mode, or I could say yarn, but that is default. Or if it was a Spark standalone cluster, then I could be giving something like this, your host name, and then your port. So you could do all of these options by specifying minus master. I could also specify how many executors I need, how much memory per executor, how much cores per executor I need. And I could also say deploy mode as client, which basically means my driver will run on this machine. However, my execution of application will happen on cluster nodes. I can also say deploy mode as cluster, which basically means my driver will run on one of the nodes of the cluster. You could submit your application, and then based on whatever arguments you have given, your application will be submitted on the cluster and it will run. So you can have your application running. So as I said, you have an application which has a driver, and it also has either Spark session or Spark context, which takes your application request to the resource manager. Now, if your application is completed, you can always come back and look into the Spark history server or Spark UI. If I choose this as my application, which I have run, I can go to executors, and that shows me that there was one for your driver. Now that was running on this particular node, which is my client node. Then I have my executors on my other nodes, which are nodes of my cluster, which used one core, which ran 2 tasks for the partitions which they were working on, and there was some shuffling involved as we were doing a word count which uses reduce by key. So when you run your application, your yarn or your cluster manager, such as resource manager, negotiates the resources to the slave processes. Your worker node basically will have the resources available for any kind of execution. Now, as I said, your resource manager will request for containers. your worker nodes will approve those containers. And then within those containers, you will have the executor which will run, which will take care of the task to process the data. So what is a task? It is a unit of work for the data set which has to be worked upon. So your RDDs which get created have partitions, and for every partition you have a task which is taken care by the executor. So the data is loaded into the RDD when an action is invoked, and then your task is worked upon by the executor. So what does it do? It basically gets the data into the partition of RDD and then does the execution as a task on that particular partition. Results are then sent back to the driver, and you can also have your output saved on the disk. So this is how your application runs. Whenever you run a particular application, you can always go to your web console and scroll or look into the logs for more information. So here our application was run, and we can see right from the beginning here when we talk about Spark submit, which is done here. It says running Spark version 2.2. It basically then will see that there will be a driver which will be started. You can further see that it does some memory calculations. It then starts a Spark UI. And here we can see that requesting a new application from cluster with 4 node managers, verify our application has not requested more than maximum memory capability of the cluster. So the container sizing at the cluster level is 3 GB per container, and your application should not be requesting for a container bigger than that. It starts a application master container with specific amount of memory, and then finally your execution starts. If we scroll down and look into the logs, we will see where my driver runs. It will also show you how much memory was utilized, and it will talk about DAG scheduler, which is taking care of execution of your DAG, that is series of your RDDs. And finally, you will see the result getting generated or saved. So this is how you run your Spark application. This is how you can see your Spark applications in History Server or Spark UI. And this is how overall Apache Spark works, utilizing your cluster manager help, getting the resources from the worker processes, and then running the executors within those. So when you look at Spark, and we have learned about these different components, so you can find a lot of use cases by just going to Google and typing in companies using Spark. Now here there is one of the case studies. So OpenTable, now that's an online restaurant reservation service which is based in San Francisco, California, and their service covers more than 30,000 restaurants in US, and they have expanded to different countries. Now what OpenTable had was that they were facing issues while giving restaurant recommendations to the customers, and in turn also analyzing the customer reviews. They started using Spark basically to tackle the challenges or problems they had. So OpenTable uses Spark for training its recommendation algorithms. So the algorithms which would be basically recommending restaurants and the services to different customers. And for that, OpenTable uses Spark. Now they could then suggest restaurants to book. OpenTable also uses Spark for natural language processing of restaurant reviews, which can then give new topic models. So with all this, OpenTable has achieved 10 times speed enhancement. It has helped them by reducing the runtime of their machine learning algorithms from few weeks to just a few hours, and that has obviously increased their productivity. So these are your different components. You can look into the demos where we talk about Spark MLlib using Scala or Spark MLlib using Python. You can explore more on these different components such as Spark MLlib, Spark Streaming, Spark SQL and data frames, and also your core API or the basic building block of Spark, that is RDD. In the last video, we learned about the equation of line and how it can be represented on a graph. We also learned on using Scala and ML basically to work on a linear regression problem. And here I will give a quick demo on solving the similar problem, or in fact the same problem, using PySpark. Now here I have two machines running. So these are my machines where I have a Spark standalone cluster, And if you have a look at this, I'm also running a Hadoop cluster, although I intend to just use Spark here. So I have a Spark master and Spark worker running on this machine. And if I go on to my second machine, I have a Spark worker on this. So I have a 2-node Spark standalone cluster, which can be used to test our functionality of PySpark. Now we all know that we can always look into the Spark directory and look in the bin, which basically has the binaries. Now last time we were using Spark shell to basically run Spark and also try out ML, or also your MLlib, which are your basically the components or packages to work on machine learning problems. Now here we have PySpark and we can be using this. So let me just go back here and we can bring up PySpark. Now normally when you are trying to use PySpark, it would be using Python, which is installed on your machine. And if you check here on my machine, it shows Python 3.5.2. Now by default it would be Python 2.7, and you can do some steps so that you can set your Python to 3.5. Then you can install some modules which would be useful when you're working on a machine learning problem. So let me just show you what steps you need to do here. And what you can do is on all your worker nodes, you can just repeat these steps. Basically, first you can check what version of Python you have. Now in my case, I had in my user bin, I had 2.7, 3.5 and so on, although my Python was set to 2.7. So what I did was I did update alternatives and update alternatives to set my Python as 3.5. I checked my Python version if it was pointing to 3.5. Then I did a apt-get remove Python pip if it was installed earlier. I then installed Python 3 pip, which would then be used to install, say, packages NumPy, which we would be using when we are working on machine learning libraries. Now, once this is done on both your nodes, you can check if both your nodes have Python 3.5.2. If you have a Spark standalone cluster, then repeat this on all the worker nodes. If you intend to use Spark with Yarn, then make sure that on every node where you would want your Spark application to run, make sure that Python is upgraded to, say, the latest version. In my case, I'm using 3.5, and then install your Python pip, and then you can import modules such as NumPy. Now, once all these steps are done, I can basically also show you what's in my bash RC here. And this shows that I have set my Spark path to user local Spark. Now that's where I have installed Spark, and I have also pointed it to the binaries. So technically speaking, I can give my Python commands from anywhere. Now here, I'll just do a PySpark. Now that should basically connect to Spark. And this is where we will be using PySpark to work on a linear regression problem. Now, in my previous video, I explained how you express equation of a line. What do you mean by linear regression? What does it mean when you want to plot a regression line? That is basically looking into your dependent and independent variables and trying to get a regression line, that is doing a regression analysis, finding out your residuals, the points which do not lie on your regression line. Also looking and finding out your intercepts, that is the points which lie on the graph or on the line, or you could say X or Y axis, and then also your gradients. Now, how do we solve a similar problem using PySpark? Now, obviously, we will have to import some packages for that. So first thing what we will do is we will import from your pyspark.ml.regression. I would import linear regression. Now we know that Spark has different components and it also has support of these libraries for ML, so machine learning algorithms, and these algorithms are already there. We just need to use them. So import this package. Now once that is done, then we can work on a data set. Now in my case, I'm going to use the same data set which we used when we used Scala. That's also updated in the GitHub link, which I will show you towards the end of this demo. Now here, if I look in sample files, I have various files and I would be interested in working on this e-commerce customers.csv, and we can have a look at this one. So I could basically look into this data set. This is a CSV data set which has various fields such as email, address, avatar, and we have seen the same data set when we solved linear regression problem where we use the same data set, but we did use Spark shell and we use Scala programming. Now here we intend to use PySpark and Python. So we have certain columns or certain fields here such as average session length, time on app, time on website, length of membership, and these could be considered as the features which we would be interested in. And then you have one more field called yearly amount spent, which we would then be using as a label. So this is the data set which I would be working on, and this is in a particular folder. So what I would do is I would want to create, say, a data frame out of this data set, and let's do that. So first thing is I will use this wherein I'm creating a variable called data set, and then I'm going to read in this CSV file. So let's go back to my PySpark. So I'm saying data set. Now we already know that similar way we do it in Scala. So here in PySpark, we do a spark.read.csv. We could have also done read.format, specified a format as CSV, but here I'm straight away using this file. Now remember, if you are using a Spark standalone cluster, then you would need the file to be existing on all your worker nodes. In my case, I've taken care of Python being upgraded, the modules such as NumPy being downloaded, and also this file exists on all the worker nodes. I'm also doing an infer schema to basically understand the schema of the file, and I'm using header as true, which basically means the first row of the file would be considered as header. Now let's go ahead and do this, and that creates my data set, which we can always do a show and look into what does my data set have. Now once this is done, using your PySpark, we can always do a dataset.show. Remember, it shows you only 20 rows, but then we will get an idea what we have in our data set. So you see, all my CSV fields have now been converted into a row and a column format, that is data frame, which has email, address, avatar. And as I explained earlier, these fields do not have an impact on the yearly amount spent. However, you have other fields which we are interested in, and that are average session length, time on app, time on website, length of membership. Now this is my data set already created with the respective fields which we would want to use to solve a linear regression problem. Here, as I said, we would be interested in finding out the relation between independent and dependent variables. We would look at the data, and as I said, your yearly amount spent field can be considered as label, and we already know that for supervised learning, your labels play an important role. Now let's go further, and what we will do is we'll import two other packages here. One is vectors and one is vector assembler. Now we know that when you want to work on a machine learning problem, you would have to use some feature extractors like vector assembler and also convert your data in the form of vectors. Let's copy this and basically import vectors and also import vector assembler. Now whenever you're working on a machine learning problem, we would be using different kind of feature extractors. Now to look into more detail about vector assembler, you can go into Spark documentation and you can click on classification and regression. You can then be looking into some examples of linear regression. What you could also be doing is you could be searching for, say, feature extractor. For example, we could go here, extracting, transforming, and then here you can search for vector assembler, which is over here, and that basically gives you an explanation if you would want to learn more about it. I explained this in the previous session. So vector assembler is a transformer that combines a list of columns. As I said, some of our columns are the features into a single vector column, and it is basically used for combining raw features and features generated by different feature transformers into a single feature vector. And machine learning would expect the data to be in the form of vector so that we can then train our machine learning models such as say logistic regression, decision trees, and so on. Now you could read more about this vector assembler and other similar feature extractors here. Let's go back to my terminal, and what I would do is I've already imported the packages. Now what we can do is, once this is done, we will create a variable called feature assembler, and here I would be using vector assembler, which would then consider these columns which I mentioned as features, and I would mention them as the input columns, and the output column could be called as output features. So basically my vector assembler would combine all these features as one column with comma separated values. So let's do that. Now once this is done, we have our feature assembler, and at any point of time you can then do a transform, or you can basically save this in a variable. So let's consider this output equals feature assembler, which we just created, and we will transform our data set based on this, and then we will have a look at our output variable. So let's do this, and then I can do a show, which should then show me that I have input independent features. Now I have all the fields as we saw in our earlier data frame, but then apart from my yearly amount spent, I also have independent features, which is basically a consolidation of values from these 4 fields, or 4 fields which have our features. Now once that is done, we can then basically create a new variable where we would want to just select the independent features and the yearly amount spent. So these are the 2 variables in which we would want to see the relation. So let's do this, and I have created a finalized data which is output.select, and here I have just considered these 2 columns, that is yearly amount spent and independent features, which is nothing but a vector of all the features. Now once this is done, we can always do a finalized data which we have created dot show. Let's do this, which shows me my finalized data, which has only these 2 columns. So independent features is basically the set of features which have a label or a response which is yearly amount spent, which can also be used to train our data set or train our model, and also then test it against a model for making some predictions. Once this is done, let's do this, where I will say train data comma test data, where I would want to split my data into training and test data set, so that training data can be used to train your model, and then test data can be used to validate or evaluate its efficiency. So let's take this train underscore data, test underscore data. I would work on finalized data. I would do a random split into 75-25%. So let's take this one, and here we have done this. Now what we can do is then we can use our linear regression algorithm. So I'm creating a variable called regressor. I will do a linear regression. Now that needs the features column, which is our independent features, and then the label column, which is yearly amount spent. Let's take this, and then let's create this variable called regressor. Now once this is done, we can then do a fit method on our training data, which we have created in the previous step. So let's take this, where we will use the fit method, and once that is done, we can then find out our coefficients, our intercepts, and also do some predictions. So let's work on this, and I will say regressor dot coefficients, which should show me set of coefficients here. So this is my coefficients. I can also get intercepts, which is basically the points which lie on the x or y axis, and that gives me an intercept. And then I can also get the predictions. So for predictions, what I can do is I can basically create a variable called pred results, and then I can get my predictions out of it. Here I am using a evaluate method on my test data set. So I would do a pred underscore results, and then I use my regressor, which we created here. And then what we could do is we could just say regressor.evaluate test data. And once this is done, then we can pull out our predictions. So what we can do is we can go in here and we can just do a pred results. predictions.show. So this gives me the prediction, and if you look at the values, these are pretty much close when you compare your yearly amount spent and the predictions what we have made based on the features. Now we can always look at more values by just adding in a value here, and we can see how close have we got with our prediction in comparison to the labels which we used. So we used the training data and then we evaluated, or we used the evaluate method to find out the prediction when we were working on our test data set. This is a simple example of linear regression where we have used PySpark, and then either we have listed down our predictions, or we have looked at the coefficients, we have looked at the intercept, and we have worked on a comma separated value or comma separated file which has set of features, a column which explains the response or labels, and then we have been able to do the predictions on this. This is a simple example of linear regression using PySpark. For more details, you can always look at the Spark's website, and basically you can find out some more interesting examples when it comes to your linear regression or any other problems which you would want to solve. And welcome to this quick tutorial on using PySpark to work on a regression problem. Now, in my previous videos, you might have seen how we used Scala programming and we used Spark shell to basically work on a regression problem such as linear regression and logistic regression. And if you look at the previous video, I have also explained how logistic regression works, how you work on a sigmoid function, or basically if you have your data points which would then relate to your S-curve using a threshold, how would you do your predictions? Now here I have a data set in sample files, and that's called credit card. So let's look into this, and this is the data set which I would be using for the logistic regression problem. Now basically if we look into this data set, this basically has information, it has different fields. So there are 28 fields, that is V1 to V28. There is a time column, there is also amount and class, and we would be using this data set to solve a logistic regression problem. Now when we talk about logistic regression, we know that we would be interested in binary classification, which is basically resulting in yes or no, or a binary value such as 1 or 0. Now how do we work on this? Using PySpark, which is also available. So on my machine, I already have a Spark standalone cluster running, which has one master and two worker processes. Now we have used the same Spark standalone cluster to work on our linear regression problem or logistic regression problem using Spark shell. I've also shown how you can be using PySpark to solve a linear regression. And here I would give you a quick demo on using logistic regression or using your PySpark to solve a logistic regression problem. Now, for that, as I mentioned earlier, you will have to make sure that your environment is set up correctly. That is basically repeating all the steps if you have not done, which are shown here, basically to make sure that you have your Python set up correctly. Then you will have to install the Python modules. Now, if you would be working on a linear regression, you could be installing NumPy. And similarly, if you intend to work on, say, a logistic regression problem, also you could use pandas, which could then be used to visualize the data if you would be wanting to visualize the data and understand more about it. Now let's go ahead. Now on this machine and the other machine, I have already done install pandas and also install PySpark SQL. Now you can also have a look at this link which talks about Arrow. Now that could be used when you're working with pandas, and if you would want to transform your data frame or a Spark data frame into a Python data frame for further analysis or further visualization. So the first thing what we need to do is we need to basically start our PySpark. So what I would do here is I will just go for PySpark. Now my Spark standalone cluster is running, and PySpark is basically the Python's way of working with Spark. So we will still have to load the data in memory so that we can create a Spark data frame out of it. And for that, this is the first step where I'm doing a read.csv. Now I already showed you a credit card CSV file which has basically transactions and so on. Although this is an anonymous file and it does not have relevance to any real data, but then this data is what I would be considering. So let's take this one and go ahead and create a data frame to begin with. Now once the data frame is created, you can do a print schema. You can look into the data to see what your data frame contains, and once this is done, you can always look into your data frame. Remember, if you are using a Spark standalone cluster, all the Python related installation has to be done on all the nodes. Your data set has to be existing on all the worker nodes. Now here we can do a df.show to see what our data frame contains. We can also do a df.print schema and basically look at the schema which shows me the different columns which are available in this particular data set. Now what do we need to do once this is done? We have already created a distributed data frame by loading the data set, and we have used PySpark for it. And what are we interested in? We are interested in finding out or classifying the transactions as fraud or not fraud. So basically we are looking for result in form of binary, that is yes or no. Now we have these columns as I showed you here, V1 to V28, and these columns are transformed features which are extracted from the main data set. So here data is anonymous and it does not have relevance to actual or real data. Now what do? We can always look at the length of the columns in my data frame. So I could do this, and we can see that there are totally 31 columns in our data frames. Now this is just a list comprehension instead of writing all the 28 columns. So we could do this, and we could be looking at some of the columns, and we could just do this to have a quick overview of what our data or what our columns containing the feature have. Now, as I said, you could be optionally using pandas. That is, if you have installed pandas, you could be converting your data frame into a panda data frame. You could then visualize all your columns, how they are varying across rows, and for which we can use matplotlib. However, that is not within the scope of this session, but you can have a look. I have given you the code wherein you can import matplotlib, and then you could be using matplotlib to visualize the data in these different columns, just to get an idea of what are the spikes, what are the different variations of transactions, and if we see some kind of pattern. Now, coming to specifically logistic regression, we will have to import specific packages like what we did in Spark Shell. In the same way, we will have to import these packages over here. So let's get these packages. Let's copy this and let's have all these packages imported. So which we will need for our logistic regression code and to solve basically the problem using logistic regression. So let's get these packages. I have already documented it here so that I avoid typing while I'm giving a demo, and just import all the relevant packages such as binary classification evaluator, logistic regression, your pipeline, you have your tokenizer or hashing TF, you have your parameter grid builder, and also cross validator, which we will be using for our use case here. So let's import these packages to begin with. And once this is done, then we can look at the columns in the data frame. We would not be interested in the first column which talks about time. We would not be interested in the last column. So we would just be importing all these packages, and then you can just do a slicing using your df.columns, and that shows you your columns from V1 to V28. And then we would also be interested in the amount column. So classification is something we are interested in. So class is what we have left. We have left out the time, which is the first column. So we are looking at these columns. Now, what do we need to do further? So if, as I mentioned, if you would be using pandas, you could be doing visualization. We could have a visualization technique and we would have noticed some kind of patterns or spikes. And for that, I would suggest if you are using something like a notebook, which is integrated with Spark, it will be really useful. Or you can have different ways wherein you can use MLlib and do the visualizations of your variations. Now we could use ROC curve instead of accuracy metrics, which to basically help us in determining and classifying a transaction as fraud or not. What we would be doing is we would be just using the column 1 onwards till the amount only, and then I would be interested in casting each column into float. So for that, you can basically get this PySpark SQL function, and let's import this. Now, once this is done, then we can basically have a function where for the column names in your data frame, we would be using a with column method and we would like to cast it into float. So this will be useful for our further processing of the data. So let's take this for column and basically do this, and then you have to use the Python, so you have to go for indentation, and let's get this one here. And once this is done, so you would have casted your columns as float. Now once that is done, then we would be interested in renaming our columns as labels or the class. So we basically need to get the features and also the label which is used in supervised learning. So let's take this and let's have the columns renamed. Now once that is done, you can always look at the columns. How does it look like? So we have these columns which we are working on, and now I would be using vector assembler. Now I have explained this earlier. So vector assembler is for extracting your features, and what we would do is we would create a variable called vector assembler. Here my input columns will be all the feature columns, and they can be grouped together by calling in one column which is features. So this is what I want to achieve using vector assembler. Now you know for your machine learning, it would always like the data in the form of a vector or a single vector of features, and vector is also a list, right, where your data is vertically arranged. Now once we have used vector assembler, we can then do a transform on our data frame using your vector assembler, which we have created in the previous step. Now once the transformation is done, then you could be just selecting the two columns. One is the features, which is nothing but a consolidation of all your 28 columns, and your label, which is nothing but the response. Now once that is done, we can again look at what does our select show by doing this. It's a simple way of just looking what you have been doing. Might be look at particular fields and see what it shows up. Now once this is done, then comes using our logistic regression, where we will specify how many number of iterations, what is the feature column, what is the label column. So let's create a variable called LR, and I'm using the logistic regression here, the algorithm which is already inbuilt with Spark comes up with. Now once this is done, we can then create a model by using the fit method on our transformed data frame. So let's take this and we create a model by doing a fit method, which basically has to work on our transformed data set which we have created here. Now once this is done, then we can proceed. So what we would want to do is we could be doing this where we are creating a model. We can print the model summary and we could look into area under curve, right? Now that is one option or one way of doing things. But what we would be doing is, instead of going for this one, we would be using a cross validator, right? Now cross validator comes within your tuning. So you can always look into this link which talks about ML tuning, and here it talks about how to use MLlib's tooling for tuning your ML algorithms and pipelines. So using a built-in cross-validation and other tooling allows us to optimize hyperparameters, right? So one of the important tasks in machine learning is model selection, or using data to find the best model or parameters for a given task. And this is what we mean by tuning. So that could be done for individual, that is estimators, using logistic regression, or an entire pipeline which includes multiple algorithms. So you could read more about cross-validator, how it works, what is cross-validation, wherein you split the data into a set of folds which are used as separate training and test data sets. Now this is what we have seen even in linear regression. So you could be using cross-validator, which could be generating your training and test data set, which could then be used to test the accuracy of our problem solving or our model. Right? So read about more about cross-validation on this particular link. Now coming back here, what I would be interested is, rather than creating a model using fit method and then looking area under curve, as I said, I would be interested in going for cross-validation. So cross-validation is usually good as we can have values fit on the complete data. Thus we can test how our evaluation metrics is working on complete data set and how good are parameters for the model. Now in this case, we need certain things. We need an intercept so that we can fit intercept for logistic or no. You need elastic net parameter, and that is basically your regularization of parameters used in ML, so that your one of the parameters does not dominate over other parameters, or you don't have any kind of overfitting. Now how do we do that? So for that we will use a parameter grid builder, and I'm saying add grid. Now here I'm giving regularization parameters. I'm then doing a fit intercept, which is being provided with both values, that is true or false, and also your net parameters. So let's take this and let's go ahead and take it to the next level. Now once this is done, we basically have to use the cross validator. So in this cross validator, we would be specifying an estimator, what we would want to use. So that's our logistic regression. We are giving the parameter map, which is param grid we built in the previous step, and we are using a binary classification evaluator. We can also specify how many number of folds we have here. So once this is done, you are basically creating a variable which is using cross validator. Now once that is done, then we can basically use cross validator to fit, or use the fit method on our transformed data frame, and we can create a model out of it. So wait for your model to be created, and then to check your accuracy metrics, we can simply do an average metrics. So this is a simple example of using logistic regression to solve a problem and to look into your data to classify it in the form of binaries, that is yes or no. And we are using PySpark to work on our problem. Similarly, you can also look at the previous videos where we have done a logistic regression using Spark shell, and we have used basically Spark shell and Scala to solve a business use case. So let's just give it some time where it is creating this model. Now that might depend on your system performance, and you can always look at the result of this. Remember, your Spark MLlib has different algorithms already inbuilt to solve your different data science kind of problems, or basically using your different techniques to solve your different problems. So once this is done, let's come back here. And so it is just trying to use the cross validator on our transformed data set. Once this is done, the last step would be to look into your average metrics. This is done, and you can always do average metrics to see your metrics and to check your accuracy on your problem. Now, as I explained earlier, when you have your Spark running, you can always go to the UI to see more information, and here I can go into this particular link which shows me the application which was running. It's a PySpark shell. You can look at an application detail UI which will give you the DAG. It will tell you what kind of transformations happened, and basically you can click on any one of these to see what it does. You can always look at how many tasks were run, what kind of internal steps were being done in basically processing this particular data set. You can also look at the executors. You can look at other information if there was something which was cached. So we see there was something cached in memory in a deserialized format, and that was probably being used for your further processing steps. So this is a simple example of using your PySpark to use or to work on a logistic regression problem, work on your data set to classify it with binary values. Here we will learn on what is Spark streaming data sources, features of Spark streaming, working of Spark streaming, discretized streams, caching or persistence as we call, checkpointing in Spark streaming, and we will then have a demo on Spark streaming. So let's learn on what is Spark streaming and what it is capable of. So it's an extension of core Spark API that basically enables scalable, high throughput, fault tolerant stream processing of live data streams. Now data can be ingested from different sources like Kafka, Flume, Kinesis, or TCP sockets, and then it can be processed using complex algorithms expressed with different kind of functions such as map, reduce, join, and window. And when we have the data processed, that data can be pushed out to your file systems, databases, and live dashboards. So if we look on this image, we can clearly see that we would be working on a input data stream which goes into Spark streaming component of Spark, which gives us batches of input data, or you could say the streaming data is broken down into smaller batches, which would then be worked upon by Spark core engine, and you have finally batches of processed data. Now, when we talk about Spark streaming and the data sources, you could have streaming data sources coming in from Kafka or Flume or say Twitter API, or also with different formats such as Parquet. You could also have static data sources coming in from MongoDB, HBase, MySQL, and Postgres. So when we talk about Spark streaming, it receives the input data streams, divides the data into batches, which can then be processed by Spark engine to generate your final stream of results again in batches. So your Spark streaming actually provides a high-level abstraction called discretized stream, and we will learn about that, or what we call as D stream, which represents a continuous stream of data. Now when we look at your different data sources from where the data can come in, Spark streaming would take in this input, and then you could have even your MLlib component which could be used. That is Spark's component to build machine learning algorithms, wherein you can train your models with live data, and you can even use your trained model. You could be also going for structured processing or processing the data which is structurized, and that could be done by using Spark's components, that is Spark SQL, which has data frames and data sets. So you could process your data with data frames, interactively query with SQL when Spark streaming is working on the data which is constantly flowing in. Finally, the data which is processed can be stored in your distributed file system such as HDFS or any other NoSQL or SQL-based database. Now, when we talk about Spark streaming, it is good to know some of the features of Spark streaming. And here you have some of the features. So it enables fast recovery from failures. While it is working on streaming data, you have better load balancing and resource usage. And you can also combine the streaming data with static data sets and perform interactive queries. Now, your Spark streaming also supports native integration with advanced processing libraries, and that is one of the benefits users can have when they are using Spark streaming. Let's learn about working of Spark streaming. So, as I mentioned earlier, at one end, you have your data streams. Now, those data streams are then caught or received by your receivers, which we have to enable in our application. Your data streams or streaming data, which is constantly getting generated and flowing in, is broken down into smaller batches, which will then be processed by Spark. So you would have your final processed results. Now, if we look at the bigger picture here, we will talk about live input data streams that could be divided into smaller batches. And when we say batches, these are batches of input data as RDDs. So Spark streaming performs computation expressed using these streams. It generates RDD transformations, So you would have your Spark batch jobs to execute RDD transformations, which would give you your final processed result. Now there are various examples and we'll look at examples later. So once your Spark streaming works on breaking the input into smaller streams, it can then process the data, finally giving you batches of your result. And that is again on the streaming data. Now, what is these D streams? Let's understand about D streams or discretized streams. So that's the basic abstraction provided by Spark streaming. Now it represents a continuous stream of data, either the input data stream received from the source or the process data stream generated by transforming the input stream. Now here, if we look at the D stream, we would say you would have series of RDDs or series of transformations applied on the data which is flowing in for a particular time frame. Now here we say data from time 0 to 1, and that would result in some of the transformations which you would perform on the data when it has come in between this time zone or time frame. You would have again data from time 1 to 2 and so on. So that's how your Spark streaming works. So if we look at your different transformations, now there could be various transformations which could be applied on your data. So this is something like your streaming data which comes in. You would want to say have a receiver which monitors a particular socket or a particular port and looks for data coming in. We would also define the time interval, and for that time interval the data is taken. So that's a smaller batch or a D stream on which you could have your processing done. Now within your application you would have series of steps which are nothing but transformations which would be performed on this data within this time frame, giving you a result which could be stored, which could be seen on your console, or which could just be pushed further for processing. And this keeps happening at regular time intervals, whatever you have specified, till the Spark streaming application continues. Now, when we talk about Spark, we already know that there are different kind of transformations which can be applied. So you have map transformation, wherein you have map and then you pass in a function which basically says you would want to perform a function on every element. So when we say map function, that would return a new D stream by passing each element of the source D stream through a function which is passed. Similarly, it is for flat map, where you would be passing in a function. You would want to perform a flat map transformation on the data stream or D stream which comes in. So each input item can be mapped to 0 or more output elements. You could be doing a filter wherein you return a D stream by selecting only the records of the source D stream on which the function returns true. So filtering is used when you want to run a transformation where you would want to look at the input data for a particular time interval, as I mentioned earlier, and you would want to filter that data as per whatever your function is applied. Now you could be doing a union where you could basically be having a union of multiple D streams. So this would return a new D stream that contains union of elements in the source D stream and a other D stream. You could be doing a transform function that contains the union of elements. You could be doing a count. You could be doing a join. So these are some of the transformations which can be performed on your D streams. Now there is also a concept of windowing, and that is basically to process the data for a series of time intervals. So when I mention windowed stream processing, I'm saying Spark streaming would allow you to apply transformations over a sliding window of data. Now this operation is called as windowed computation. Let's see how it looks like. So if you have your original D stream, which is basically your data coming in, now that would be looked upon for specific time intervals such as time 1, time 2, and then you could be doing a windowed computation, which could basically mean that I could have a window which is a series of these time intervals on which you would want to perform series of your RDD transformations. So you have a window D stream at time 1, then at time 2 and time 3. So that could be one window wherein you would want to get an output. So here we see window at time 3. Now you could also have another sliding window which would take your time series, and we have time 3, time 4 and time 5 where you could be performing the series of transformations. So this is usually helpful where you would not only want to process the data at particular time interval, but you would want a consolidated processing for series of intervals. And that's what we mean by windowed computation. Now, before we understand about caching and persistence, we can talk a little bit more on windowing. So if one would want to understand the window stream processing, or as we say, Spark streaming's feature of windowed computations, we need to think it as applying transformations over a sliding window of data. Now, as we see here, every time the window slides over a source D stream, the source RDDs that fall within the window are combined and operated upon to produce the RDDs of windowed stream. Now, in this specific case, we can say the operation is applied over last 3 time units of data and slides by 2 time units. This shows that any window operation needs to specify 2 parameters. One is the window length, which is basically the duration of window. So for example, we can say 3 as we see in the figure here, and then you have a sliding interval, which is basically the interval at which window operation is performed. So these 2 parameters must be multiples of the batch interval of source D stream. So that's what we do when we talk about window. Now there are various other transformations which can be applied, or window based operations which can be done on your D streams. Here to talk a little bit more on D streams, which is, as I said, it's a basic abstraction provided by Spark streaming. It represents just remember it as a continuous stream of data. Now either the input data stream received from source or the processed data stream, which is generated by transforming the input stream. So a D stream is represented by, you could say, a continuous series of RDDs, which is Spark's abstraction of a immutable distributed data set. So any operation applied on a D stream, it is basically translating to operations on the underlying RDDs. Now, for example, we can say converting a stream of lines to word. The flat map operation is applied on each RDD in the lines. Now D stream to generate the RDDs of your words D stream. So when we talk about your discretized streams, understand that you would have a series of transformations which would be applied for this time interval, whatever has been specified. Now when you talk about your streaming or Spark streaming architecture, as I mentioned here, that is your receivers. Now that plays a very important role here. So your input D streams or data streams are representing the stream of input data that is received from your streaming sources. Now we could have different kind of data and we could be doing different kind of transformations. So your receiver is basically an object which receives the data from a source and stores it in Spark's memory for processing. And that's the main role of your receiver. Now Spark streaming provides 2 categories of built-in streaming sources. So you have basic sources, that is sources directly available in streaming context, which is a class we learn about it, such as your file systems or socket connections. So those could be your basic sources from where the data is coming in. You could have advanced sources like your Kafka, Flume, Kinesis, etc. And they would be available through extra utility classes. So your receiver is going to be looking into the data which is constantly getting generated and then basically forwarding it for processing by your Spark streaming. When we talk about your Spark streaming, one more important aspect is basically understanding the caching and persistence. Now, as we know from the Spark core engine, or as you should know, that RDDs are, say, your logical steps, or RDDs are created when you perform some transformations. And these transformations or these computations or these RDDs can be cached so that it can improve the performance of your application. So the computed RDDs or the RDDs which are result of performing some transformations, they can be cached so that they can be reutilized down your application for your further processing. So when we talk about your caching and persistence, D streams also allows developers to persist the stream data in memory. So similar to your concept of RDDs, D streams can allow you to persist the particular streams data in memory. Now that is by doing or using your persist method on a D stream, which will automatically persist every RDD of that D stream in memory. It could be every RDD or it could be specifically chosen RDDs. Now, this is really useful if the data in D stream has to be or would be computed multiple times, say in your application. So for example, if we say window-based operations like reduce by window, reduce by key and window, wherein you have group of operations being done, or you could have state-based operations like update state by key. Now in any of these cases, your D streams generated by say window-based operations are automatically persisted in memory without the developer calling for the persist method. Now for input streams that receive data over networks such as Kafka, Flume, sockets, etc., the default persistence level is set to replicate the data to 2 nodes for fault tolerance. Now, one thing which we should remember is, unlike your RDDs, the default persistence level of D streams keeps the data serialized in memory. And that we can discuss again further about your serializations or deserialization. Now, one important aspect which takes care of your fault recovery is checkpointing mechanism in Spark streaming. Now, when I say checkpointing, a streaming application, as in real scenario we would want, must operate 24/7, and if the streaming application is constantly running, then there has to be a mechanism which can make your streaming application resilient to failures, which can be unrelated to your application logic. So Spark streaming needs to do the checkpointing. It needs to checkpoint enough information to a fault tolerant underlying storage system such that it can recover from failures. So your checkpointing is the process to make streaming applications more fault tolerant or resilient to your failures. Now, this is usually used when you would want to recover from failure of a node running the driver of streaming application. Now, we know driver is existing for every application, and it is basically one which knows the flow of your application. Driver also has the context. In case of streaming application, we would have, say, the Spark streaming context, which is the entry point of your application. Now, when we talk about your checkpointing to ensure your streaming application is more fault tolerant, you have 2 kinds of checkpointing here. So you could have a metadata checkpointing and you could have data checkpointing. Now, when we talk about metadata, what does that include? So metadata includes configuration, D-stream operations, or even incomplete batches. So when we talk about metadata, it has configuration. So configuration that was used to create the streaming application. You could have D-stream operations, that is set of D-stream operations that define the streaming application, that is your series of RDDs. And then you have incomplete batches or batches whose jobs are queued but not have completed. So this would have to be checkpointed. So metadata checkpointing is used for recovering from a node failure running the streaming application driver. Now, your metadata, which has your configuration, incomplete batches, and D-stream operations, need to be saved in an underlying storage system. Now, when you talk about data checkpointing, it is mainly about saving the generated RDDs to reliable storage. That is, whatever RDDs are computed. So, saving the information, which is saving the computations to a storage like HDFS. Now, that is used in stateful transformations, combining data across various batches. So when we talk about transformations, whatever RDDs are generated, that depend on RDDs of previous batches if we are talking about stateful, and that can cause the length of dependency chain to increase or keep increasing with time. Now, to avoid any kind of increase in the recovery time, intermediate RDDs can be periodically checkpointed. And that could be done to a reliable storage to basically cut off the growing dependency changes. So if we would want to summarize, we would say metadata checkpointing is primarily needed for recovery from driver failures, whereas data or RDD checkpointing is necessary even for basic functioning if stateful transformations are used. And we should remember we are talking about stateful transformations here. So when we talk about checkpointing, now the question is, when would you enable checkpointing? Or what would you do to enable checkpointing? So checkpointing must be enabled for applications with different kind of requirements. So for example, if you are using stateful transformations where one series of RDDs depend on the result of your previous batches, So something like update state by key or reduce by key in window. Now, if these kind of operations are used in your application, then checkpoint directory must be provided to allow for periodic RDD checkpointing. When we say about requirements, then recovering from failures of the driver, which is taking care of your application, metadata checkpoints should be used. When we talk about simple streaming applications without the stateful transformations, they could be run without enabling checkpointing, because your one batch of RDDs really does not depend on the previous set of RDDs which were done in the previous time frame. Now, recovery from driver failures will also be partial in that case when you talk about your stateless. So some might be received and your unprocessed data might be lost. But then that's pretty much acceptable when you talk about Spark streaming applications. So here we look at your checkpointing. So we say start. Now you have a checkpointing. Now whenever your application is creating a streaming context, it would set a checkpoint path, and then you would define your D stream, which is nothing but series of your RDD transformations. Your streaming context starts, which is basically your application entry point into the cluster for processing. And at any point of time, if there is any failure, you could always recover using the checkpoint which was created. In case of Spark streaming, one more thing we need to remember is that your checkpointing can be enabled by setting a directory in a fault-tolerant, reliable file system such as HDFS, wherein the checkpointing information will be saved. So we will have to add some methods within your application, like streaming context with a checkpoint and then pointing into a checkpoint directory. And in that way, we can have our stateful transformations or metadata information stored in the underlying storage, whichever we have chosen. Now that we have discussed about Spark streaming, some basics of Spark streaming, let's also understand about shared variables, or what we call as accumulator and broadcast variables. So normally when you talk about your Spark operations, such as your map or reduce, these are executed on one of the node of your cluster. And what happens is, when you talk about your operations, they work on separate copies of all variables used in the function. Now, in this case, variables are copied to each machine, and no updates to the variables on remote machines are propagated back to the driver program. Now, when we talk about read-write shared variables across tasks, that would be inefficient. So Spark actually provides two limited types of shared variables for common usage patterns, and those are your broadcast variables and your accumulators. Now, when you talk about your accumulators, these are variables that are only added through an associative or commutative operation. So Spark natively supports accumulators of numeric types, and programmers can add support for your new types. So when we talk about accumulators, they can be used to implement counters such as your MapReduce or sums. So as a user, you can create named or unnamed accumulators. Now, as we see in the image here, a named accumulator in this instance counter will display in web UI for the stage that modifies that accumulator. Spark displays the value for each accumulator modified by a task in the tasks table. Now, tracking accumulators in the UI can be useful for understanding the progress of your running stages, but we should remember that as of now, this is not supported in Python. Might be in future the support for Python will also be added. Now, when you talk about your accumulators, you can have, say, a numeric accumulator created by calling a Spark context and its method, such as long accumulator, or you could have double accumulator to accumulate values of type long or double respectively. So tasks running on a cluster can then add to it using the add method. Now we cannot, in this case, the value cannot be read, but driver program can read the accumulator's value using its value method. We can look at some examples to understand this later. Now, when you talk about your broadcast variables, that is one more type of variables. which allows the programmers to keep a read-only variable cached on each machine rather than shipping a copy of it with tasks. Now what we know is sometimes you might be doing very costlier operations like joins, where you might be working on multiple RDDs, they need to be joined, and these RDDs could also be pair RDDs, which could be key value pairs. Now whenever you're performing a join, there would be kind of two levels of shuffling. One, within a particular RDD. So if you're joining two RDDs, the first RDD, which might have data in the form of key value pairs, that RDD would have to have some shuffling where all the similar keys can be brought into one partition. And this would happen on the second RDD also, which has again key value pairs. And then if you're doing a join, these RDDs will be shipped to the node, or basically the data would be loaded in the memory, and then basically your transformations will happen. This can be a costlier affair. So what can be done is you could create broadcast variables. So for example, if we have two RDDs and we want to perform a join operation, and if one RDD is known to be smaller, then we can create a broadcast variable of the smaller RDD so that this variable itself can be shipped to each machine, and then this variable can be used for your join operations with the other RDD which is existing in the memory of those nodes. So that saves time and that improves your performance. So Spark basically attempts to distribute the broadcast variable using efficient broadcast algorithms to reduce the communication cost. Now, if, for example, you have multiple nodes in a cluster, and if you would want to give every node a copy of large input data set in an efficient manner, so Spark actions are executed through a set of stages. Now we know that. And stages are separated by your shuffle operations. So whenever we talk about narrow dependencies such as map, flat map, filter, you would not have any shuffling involved. But if you go for group by key, reduce by key, and such operations to bring the similar keys together, there would be shuffling involved. And also this applies when you're doing some join operations. So in that case, broadcast variables could be a really plus, where one set of data or RDD, which is already computed, that could be broadcasted to other nodes. So the data broadcasted will be cached in serialized form and deserialized before running each task. This means that explicitly creating broadcast variables can be useful when tasks across multiple stages need the same data, or when caching the data in deserialized form is important. So we can create broadcast variables using Spark context and its method called broadcast. And your broadcast variable can then be shipped to other nodes which can be used for your other operations. Now, when you talk about Spark streaming, it is used in various use cases. I mean, you could talk about speech recognition, you could talk about sentiment analysis, you could talk about streaming applications which would be performing some kind of analytics on the data which is coming in. It is also used widely in retail chain companies. Now, if we look at the example here, so big retail chain companies would want to build real-time dashboards so that they can keep a track of their inventory and operations. And for this, they would need one, streaming data, or data which is constantly getting generated at source, which needs to be processed on, and this information can then be populating your dashboards to give you a real-time scenario or real-time information of what is happening. So in case of an inventory dashboard, you could use then these interactive dashboards wherein you could draw insights about the business, and that's what retail companies are doing. So how many products are being purchased, or products that have been shipped, or how many products have been delivered to customers, and this kind of information would be good to capture in real time. So when the streaming data is basically being processed. So at one end, you have your data which is getting generated. That might be based on the sales which are happening. That might be based on the products which are being shipped, or that might be based on the acknowledgement that the products have been received. Now, while this data is getting generated at various sources, it can be subjected to a Spark streaming application, which will look into the streaming data, perform series of transformations which you would want to process the data at regular time intervals, and then pushing it to your dashboards or to your storage layer, wherein it could then be used to answer such questions. So when we talk about Spark streaming, it's an ideal choice to process this kind of data in real time, and there are various use cases. So at one end, if you see, you have an input stream which shows the product status, that is how many products were purchased or shipped or delivered. Now this would be then handled by your Spark streaming and also your Spark core engine, which would then process the data to give you an output stream which gives you a status, such as what was the total count of products which were purchased, products which were shipped, and products which were delivered. So this was a quick and brief introduction to Spark streaming and how it works. Now we can also see how Spark streaming works, or how we create an application. For that, what we can do is we can basically set up our Eclipse to have your Scala based Spark applications. And for that, what you could do is you could have your Eclipse, which can then be having a Scala plugin added to it. Now, if somebody would want to look at the Scala plugin, then you can always go to scala.ide.org. And this is the place where you can scroll towards the bottom. You can click on stable, and that basically also shows you a video how Scala plugin can be added to your Eclipse. It also tells from where you can get the Scala latest release, and this can be added to your Eclipse. So in my case, it has already been added to the Eclipse. I'm bringing it up here, and then you can have your applications built using your IDE. People would prefer to use IntelliJ, and that's also fine. So you could also look for videos on setting up IntelliJ with your Scala plugin. Now there are two ways. One, you can build your application, run it on your Windows machine, wherein you could have some kind of utility like Netcat, which can be used to send in some messages in a streaming fashion. You could have a receiver which looks at a particular socket at a particular port, and you could build a streaming application within your IDE, run it on your Windows machine in a local mode, which would then be looking at your source where the data is getting generated. That's one option. The second option is you could build your application, package it as jar, and then run it on a cluster. Now that could be a Spark standalone cluster or Spark with Yarn, and then you could be packaging your application using tools like SBT, and then use Spark Submit to submit your application. Now I'll show you both the ways in which you can work with streaming applications. So first is get your Eclipse and make sure that Scala plugin is already added. Now in my case, on the right top corner, I see Scala symbol that says I can be using Scala Perspective. Now here I have some projects. So what you can do is you can create a project by saying new Scala project. You can give it a name. So for example, I could say my apps 3, and then you can say finish. So that creates a project. Now within your project, what you can do is you can create a package. So for example, I could say something like main.scala and then say finish. So that creates your package. Now also one thing to remember is it would be good to change your compiler instead of 2.12 to 2.11. Normally for different environments, you might have Spark with different versions and Scala with 2.10 or 2.11. So it would be good to have the compiler change to the bundle 2.11. So we can select this project. I can do a right click. I can go to the build path. I can say configure build path, and then I can click on Scala compiler where I will use project settings and I will choose to 2.11 bundle. So that would make sure that your applications can compile. Just say OK. It might say the compiler settings have changed. A full rebuild is required for changes to take effect. Just hit on OK. So that's the first thing you need to do. The second thing is for your code to compile, it would be good to have your jars added to your build path. Now we could do that, or as I said, you could be writing your application which might not compile within your IDE, but you could package it using SBT and then run it as jar. So what I'm doing here is on my machine within my C drive, I already have Spark distribution which I've downloaded. So basically I have downloaded Spark and then untarred it. So Spark 2.4.3, I have unzipped or untarred it. I have kept it in my C, and this basically has my Spark now, within which I have my jars, and this has all my Spark related jars. So technically speaking, I can even use Windows command line and I can start working on Spark in an interactive way, or packaging my application and running it in a local mode. So you could also do this. So basically have your Spark, and then if you see on my desktop, I have a Hadoop folder within which I have a bin folder, and within which I have a winutils.exe, and this will be basically required when you want to try out your Spark based applications, whether that is streaming or data frames, to be tested on your Windows machine. So you can always search and download the winutils.exe, place it in a Hadoop folder within the bin folder on your machine. So once you get your winutils.exe, once you have your jars, what you can do is for your project, you can just say right click, you can go to the build path and you can say configure build path, and here you had add external jars. So we can select all of these jars here, which I would want to add to my build path so that my code can compile and I can test it on the Windows machine itself. I can say open and then just basically do apply and okay. So that has created my project with a package. My compiler is changed to 2.11. I have added the external jars, the Spark related jars, and that is good enough for my code. Now what we need is a streaming application which we need to build. So let me show you from my existing project how it looks like. So within your source, the same way I have main package, and here I have a streaming application. So this streaming application is to test or to work on capturing the data which is generated at this particular stream on a particular IP and a particular port, and I would want to do some series of transformations on that. So this gives me an example of doing a word count, and then I would want to print the results. I could also be saving the output in a particular location. So for this application, we need basically to import certain packages, that is say Spark streaming, Spark context, and also you have Spark conf. So these are the packages which we need to import. Now here I've created an object. I've called this fifth app and I'm saying extends app. And this is because within my project, I already have an application which has been defined as main. So if your application has been defined as main, one application is already existing, then you can just have your new objects with extending app. So we don't need to define the main method here. Now here I'm saying val conf new Spark conf. So I'm creating a configuration object. I'm setting my application name, and to test it on Windows, we will have to set the master as local, and it is advisable to give it more than one thread because you would be creating a receiver within your application that would utilize one thread. So here I'm saying set master local, and then I'm saying 2 threads. I'm also creating my Spark context, which we need to initialize based on the configuration object we just created in the previous step. Then we need to create a Spark streaming context, and this streaming context depends on Spark context, and I've given a time interval of 10 seconds. So this is the time interval which I'm setting for which I would want to work on the stream of data which comes in every 10 seconds on a particular socket. Now here we are setting up a receiver. So I say stream RDD, which is basically be Spark streaming context, and then you use your socket text stream. Now there are various methods of Spark streaming context. For example, if I just go here and if I just do a dot, it shows me what are the different options. You have file stream, you have queue stream, you have socket stream, receiver stream, and so on. So I am using socket text stream, and I would want to point it to this machine. So I'll say 127.0.0.1. I will also specify port 2222. Okay, and here once I have created my configuration object, my Spark context, my Spark streaming context with a time interval, and I have set my receiver to use the socket text stream method on this particular IP on this particular port. Now then I'm specifying what I would want to do on the data which gets generated on this machine at this particular port. So I'm saying val word counts. So I would want to work on the stream RTD, that is the D stream. I would want to do a flat map on it to split the data based on space. I would want to map every word to word comma 1, and then I would want to do a reduce by key. Now reduce by key, you can pass in specifically the function you would want to do. I could do a count of this, I could print the result, or I could even save it with an output using the Java method to create a random string attached to the output. Once you're done with this, here I'm mentioning Spark streaming context start. Now this will basically trigger my Spark streaming context to start, and it will run till we terminate this application. Now here, to run this on Windows machine, you can always look into your run configuration. And what I have done is in my environment, I basically want to use, let's say, okay, now let's look at the configuration, what you need to set. So here I have my streaming application, and let's look at the run configuration, which basically shows my application has started and it's running on the environment. So if you see here, I have added Hadoop _ home pointing to this Hadoop directory which has bin and winutils X. I have also given Spark local IP, which is 127.0.0.1. So that is my run configuration. Now if you see here, my streaming application has started. My streaming application has not yet started. Probably it is running a different application. So we can come back and check this. So we can go to run as Scala application, and let's see what it does. So it tries to connect to 127.0.0.1. So receiver is trying to do that, but it does not find anything on that particular machine, on that particular port. So my receiver is not able to find, it is not able to establish a connection. Now what I can do is I can go to my command line, and here I will go into downloads. So I've already downloaded the netcat utility for Windows, and here we can basically search for something which I have on my machine within downloads, and that is your netcat utility. So what I would do is I will come back here and I would say nc.exe lvp, and then I could say my port which I have specified in my streaming application, and I can just start this netcat utility. Now here it says listening on 222, it says connection to 127.0.0.1, and then if I look in the background, my receiver will now be able to establish a connection with this netcat utility. Now whatever I type here will be taken for processing every 10 seconds, and we would see a word count while my application is running. So let's test this. So I'll say this is a test is being done, and as soon as I pass in this message, we see that there is a word count happening for the stream of data which is coming in. We can say winters are coming, winters will be cold, and once I given these messages, we will see our streaming application which will try to work on the data which is coming in and process it and show us the result. So we can say this is a test of winters, and let's see if it continues to do the processing and shows us the out, right? So my streaming application is running fine. It is looking at the words which we are passing in, and we can say if it is able to process my data, and every 10 seconds the text socket stream is looking on this machine at this particular port, doing a series of transformations, and these series of transformations and then are seen within your console. Now in my application, if I had used word counts.save as text file, then I could also have my output getting generated at every 10-second interval, and that would get saved here. I could also decide to have my output saved and stored on a HDFS or any other storage. So this is a simple streaming application what we saw, which is using socket text stream. It is looking at this machine on a particular port where we are running a netcat utility. It does series of your RDT transformations, that is flat map, map, and then your reduce by key. And finally, we are invoking an action such as print, which basically triggers these RDTs which work on my streaming data. So this is one example. Now what I could also be doing is, this is particularly my application. Now I already have SBT for Windows installed. So I can be going into my project space. So I could say workspace. I could go into my apps and I'm in my project folder. So I could say SBT package, and this will basically then, based on my build file, which I already have within my project folder. So if you see here, this is my build file, which says name, the version, Scala version, Spark version, and the repository with the Spark to manage the dependencies for all its components like Spark Core, SQL, MLlib, streaming, and Hive. So you need to have this build.sbt file within your project folder, which can be used to package your application as jar. Now we have done the packaging and it shows me that it has created a jar of my applications within this particular folder. Now once I have this, I can basically then import this package into my cluster where I can run it on a cluster using Spark Submit. Now to run the Spark streaming application on a cluster, here I have a 2-node cluster which will then have my Spark standalone cluster. You could look at the previous videos wherein I explain how to set up a Spark standalone cluster. Now here I can go into the Spark directory, and then I could just say sbin start all.sh, which will start my Spark master and worker node. Now I do have Hadoop cluster also set up on this, but right now I'm running a Spark standalone cluster, which shows me I have a master and a worker process on this machine, and I have a worker process on this machine. So my Spark standalone cluster is running. We can always bring up the UI to see how it looks like. So here I can just be giving http://um18080. So that's my Spark standalone cluster with 2 worker nodes. Right now there is no application running. We can come back here and we can check if we have my jar file. So I've already placed my jar here. Now at any point of time, if you have your jar which has been packaged, you can always go and do a jar -xvf, and you can choose your jar to see what is within your jar, which I've already done on this machine. So if I look in the main folder, I have Scala, and within Scala, if you see, these are the different classes what we have. So my code was packaged as a jar. It has a 5th app class which we would want to run here. So what I can do is I can just be saying Spark submit, because now I would want my application to run on the cluster. So I can say class main.scala and then my object name. So I will say 5th app. Now that's my class. My jar is this one, and we will also say master, which is going to be Spark, which is running on UM1, and it listens on 7077 port. So that would basically start my streaming application. But what we would also need is, like our Windows, we would also need some utility like netcat. So basically what I can do is I can here use a netcat utility to basically connect or send in some messages for our streaming application. So let's say, let me search if I have already the netcat, which I might have used here. So let's see. So on your Ubuntu machine, you will have to install your netcat utility by saying a apt-get netcat. So here I can say nc -l, and then I can say port, which is 2222. So we can see if this is working. So this is a test, and let's see if it works. So let's start our application, streaming application, which then needs the receiver to establish a connection with the particular machine. And let's see if that is done. So here I could also be canceling this and give it a particular port. So I can say 192.168.0.18. Now the only problem is when we packaged our application, we should be specifically giving the IP and also comment out the local. So when I package this to run on the cluster, I commented out this part, and I obviously would not be giving 127 but the IP where my netcat is running. So right now let's test it. So we will say this is a test, new test for our application, and I'm sending in some messages, so it is already doing the word count as we expected it to do. And if while we are doing it, if you come back here, so you would see your application is now running on the cluster. So it is my application. It is using 4 cores. What is the memory per executor? And you can basically click on your application. Now here you can look at the application detail UI to see what is being done. So for our application, we have a streaming job running receiver, which says this is my application. It says it is running. You can basically click on this, and it says your DAG visualization, which will say the streaming job which is running. You can look at the stages if you would want to see if there are multiple stages, which we don't have because we are not doing any wider transformation. We can look at storage if we have used some persisting or caching. We can look at the executors which are being used. And one of the important things when you talk about your streaming is the streaming tab which gets activated. Now that does not show up when you run your batch applications, but in your streaming applications you have the UI shows you the streaming tab, and that basically says running batches of 10 seconds for 2 minutes 9 seconds already. Now we see the input rate, we see the receivers, we see if there is any delay in scheduling, what is the processing time, how many batches it has completed, and it basically shows me what is the processing time, how many tasks were run, and so on. So my application is running fine, and unless and until we go ahead and cancel this, my application will continue to run. It will keep looking for messages which we keep typing in. So for example, if I would want to just copy this and start again, where I would keep passing in, this is a test 1 is this, where we test streaming application, right? And I can be seeing that my messages are being processed. I'm getting a word count. So we can say winter, summer, old, winter, and you can always look at if your streaming application is doing the word count. So this is a simple way where you can run your streaming application either on a Windows machine in a local mode, or you could be running on a Spark standalone cluster, or you could also deploy your application to run on a yarn-based cluster. Now that we have seen a streaming application which does a word count, it will be interesting to also see the window-based computation or windowing operation which is supported in Spark Streaming, as I explained. And for that, we can look at a different application here which is streaming with a window option. Let's look into this, what this application does. So here I'm importing some packages, that is streaming context, your Spark and Spark context, Spark configuration. I'm also using the Spark API Java function. I'm then using Spark Streaming API, and I'm also using storage level because I also intend to have the persistence or caching done. Now here we create an application, say streaming app, extends app. We create our configuration object where we say app name, and then we set master with appropriate number of threads. We create the Spark streaming context, that's we initialize it, and then we have the Spark streaming context which depends on SC, and we have given a time interval of 10 seconds. We then set up a receiver, so we say stream RDD, which will use socket text stream like we did earlier, which will look for this particular machine at this port, wherein I'm also using storage level. So what I would want is that the data stream which would get generated here every 10 seconds should be cached in memory. Now we could use different storage levels, that is we could use memory only, disk only, memory and disk. You could have memory and disk with replication factor, so you have different storage levels. Now here we are then doing some series of transformation operations like what we did earlier. But if you see in my previous example, we just had reduce by key, and here I'm using a transformation which is reduce by key and window. Now this one basically takes the function. As I said, the windowing takes associative or commutative functions. So instead of using the shortcut way, we will be specifying our function. So we say it takes A and B, and basically it uses this function. Now here we have to give the interval, that is 30 seconds. That's my window time frame. And then within that, what will be my each interval which we would want to look at. So these are the two main aspects. One is using your window based transformation, and then also specifying your time interval for your windowing, which basically means we would still do a word count, but then here we would basically not only be doing a word count for every 10 seconds for the data which is coming in here, but we would also want to have a consolidated set of computation done every 30 seconds. So that is looking at the last 3 time intervals. Now, if you also notice, I am also doing a check pointing here, wherein I have not specified a specific directory, but what I am saying here is I would want to checkpoint, or I would want to basically save my computations for any kind of fault recovery. Now, this is a streaming application with window based computation. We are using storage level for persistence. We are also doing the checkpointing, which takes care of fault recovery. Now, to run this application, we have already set our environment variables and so on. So I can basically start this application by just doing a run as Scala application. Now, this would start my streaming application with window based computations. Now we can open up our command line where we would want to start a netcat utility. So I could go to downloads. Let me just minimize this window here. And what I can do is I can then be starting my netcat utility. So I could say nc.exe minus lvp and on a port 222. As soon as I do this in background, my application receiver will be able to establish connection to this netcat utility running on this particular port. Now that's done. So we can see if the word count happens for our 10-second interval. So let's do that. So I'll say this is my first test, and if I do this, it should give me the word count for the data which I have passed in. Now I can say this is my second test, this is my third test, and if you see here, it basically is doing this. Now if I say this is my first test again, so since we are doing window based operation also, we will see a consolidated set of transformations which happen for a window of 3 intervals. So if you see here, now my this is giving me a count, but it is not showing me totally this as 4 or say this, because it is only looking at a window of last 2 or 3 time intervals. So now it is back because it is looking at the last one. So if I say this is my test, test is done, test is done. So if you do this, it will show you the word count which is for whatever you have passed in, like test is done is twice, test is thrice. But then since windowing based operation is done, you will look at the time interval of the messages which were passed within that particular window. Now we can also, since my application is running and it is on Windows, we can bring up your Spark UI. So I can go to http and / I can be looking at my machine and the port. So for example, I could do this. This shows my streaming application which is running in, wherein I can see the window based application which is running. But what would be interesting is to look at the stages. If there is any kind of shuffling which is happening, looking at the storage should show me the persistence which we are doing. Now if you see here, it shows me that we have been persisting in the memory, what size it occupies, how many partitions were cached, and this is because of the persistence or the storage level what we have used as memory only. Now if we change that to disk, we will see our RDDs will be cached on disk. And then you can look at your streaming tab which gives you more information about your batches. So this is a very simple example. Obviously you can change what kind of RTD computations you would want to do here, whether you want to do a word count or something else, whether you want to save your processed output. Now here we are able to do that. You can always do a refresh on your project, and here what we see is we see some entries of a folder getting created, right? And we can decide whether we would want our output to be created. We can also see within this what would be containing, and since we have set checkpointing in the project folder, it would also be checkpointing temporarily the information for any kind of failure. So this is a classic example of streaming application using window-based computations, persisting your computations, and also doing the checkpointing simultaneously. We will learn about what is Spark SQL, what are Spark SQL features, its architecture, Spark SQL Data Frame API, Data Source API, Spark SQL's Catalyst Optimizer, running SQL queries, and then we can have a quick demo on Spark SQL. So what is Spark SQL? It's a Spark's model or Apache Spark's module for structured data processing. Now, it allows you to work with structured, semi-structured, and even unstructured data, but primarily with structured and semi-structured. It originated to overcome the limitations of Apache Hive. Now we know that Apache Hive is a data warehouse package on top of Hadoop, and this basically is quite extensible. It allows you to work on structured data or data which can be structurized with the various features such as user-defined functions or support of complex data types or custom MapReduce scripts and many more. However, there are a lot of limitations in terms of using Apache Hive, such as it always depends on MapReduce as an execution engine or processing framework, or it could also use Days. You would not be able to do insert, update, deletes when it comes to Apache Hive. It is more of a batch oriented operation, and basically querying with Hive can be time consuming. However, Hive is quite extensible in the way it supports data warehousing use cases. It lags in performance. As I said, it goes for MapReduce and is not really suitable when you would want to do faster querying or ad hoc querying. It does not allow you to resume a job if it fails somewhere in the middle. And these are some high-level limitations of Hive. When we talk about Spark, it performs better than Hive. Now Spark, we already know, is a in-memory computing framework which basically works on having the data loaded into the memory, that is in the form of RDDs, and then having the DAG execution whenever a action is invoked. Now, if we compare latency in terms of hours, we would see Spark is quite competitive in that with Hive and is a better performant. When you talk about CPU in days or CPU reservation time, in all of these cases, Spark wins over Hive. Now let's look at Spark SQL features and let's understand how it helps. So as I mentioned, Spark SQL is a module for structured data processing primarily. Now, unlike the basic Spark's RDD API, the interfaces provided by Spark SQL provide Spark with more information about the structure of both the data and computation being performed. Now we know that Spark has a DAG scheduler behind the scenes, and if that DAG scheduler could know what are the steps which are part of your processing application, then it would understand the steps, it would benefit from data which would be structured and thus have a better way of processing your data. Internally, Spark SQL uses this extra information to perform extra optimizations. Now, there are different ways in which you can interact with Spark SQL, including SQL and dataset API. You could be using data frames API, data source API, and also the older way, that is RTD API. Now, some of these features really make Spark SQL a compelling framework for data processing and analyzing, especially if you have data which is structured. You can integrate Spark SQL and query structured data inside Spark programs. It is highly compatible with SQL-based frameworks like Hive, so it can work on the data which is stored in Hive. It can work on the data which is stored in your RDBMSs, which are external to your big data setup, or even on the files which are stored on your distributed file system such as HDFS. When we talk Spark's integration with Hive, you can run unmodified Hive queries on existing warehouses in Spark SQL. So while existing Hive data queries and UDFs, Spark SQL offers full compatibility. Now, Spark SQL leverages the RDD model as it supports large jobs and mid-query fault tolerance. For interactive and long queries, it uses the same engine. So in terms of Spark 1.6 and older versions, we had RDD API. That is, whenever you do some transformations such as map, flat map, filter, and many more, that would create RDDs, and you can say logical steps in the DAG, which would be executed only and only when an action was invoked. Now, in terms of older APIs, we said that Spark has RDD, and when we talk about newer versions of Spark, we have Spark data frames or data sets. And when we talk about data frames, that is using an implementation of RDD, which we call as schema RDDs. Or you could say in older versions of Spark, we were talking about schema RDDs, which get created based on your transformations. And in newer versions, the same schema RDDs are called data frames. There are different ways in which you can use Spark SQL. So you could use an ODBC or JDBC connector, and then you could be connecting to your external databases, business intelligence tools, and then extract the data from your underlying data stores and process them. Remember, Spark does not have its own storage. It has various components such as Spark SQL, streaming, MLlib, you have RDDs, and you have graphics. But then Spark always relies on a storage. Now that storage could be a Hadoop distributed file system, that could be a NoSQL database. It could also be a RDBMS to which you can connect using JDBC ODBC, or it could be just your local file system on which your files are stored, and Spark can use those files and process the data within those files. Now, when we talk about your Spark architecture or Spark SQL architecture, you have basically at the lowest level, you have your data sources. Now that could be your data in CSV format or JSON format, or also coming in from external sources using your JDBC ODBC connectors. You have different APIs. So you have a data source API, we'll learn about it. You have a data frame and a data set API, which allows you to work with data. And then you have different ways in using these. So you could have a data frame domain specific language, that is DSL, or you could be using Spark SQL or Hive querying language to use one of these APIs to process your data. So Spark SQL is Apache Spark's module mainly to work with structured data. Now, when we talk about Spark SQL, it has three main layers. It has a language API. So Spark is very compatible as it supports multiple languages such as Python, your Scala, Java, even R, which is used in data science activities, and your Hive querying language. When we talk about schema RDD, so Spark SQL works on schema, tables, and records. And what it creates behind the scenes is a schema RDD or an RDD which has schema within it, which helps the DAG scheduler to understand the data and the steps which are being performed. And as I said, in newer versions, your schema RDD is your data frame, which is nothing but a representation of your data in the form of rows and columns with column headings, and you could call it as a temporary table where your data is getting stored. The third layer is your data sources. So that is your data coming in from varied sources. That could be your files in different formats such as CSV, JSON, text, Parquet, Avro, and so on. You could be getting your data from different NoSQL databases such as Cassandra, MongoDB, your HBase, or anything else. You could also be getting data directly from Hive, which are your logical structures such as databases and tables. However, the data is stored on an underlying file system such as HDFS. Now, when we talk about your data frames and data sets, so a data frame is basically a data set organized into named columns. So what is a data set? So a data set is a distributed collection of data. It's a new interface which was added in Spark 1.6, which provides the benefits of RDDs such as strong typing, ability to use powerful Lambda functions, and with the benefits of Spark SQL's optimized execution engine. So a data set can be constructed from JVM objects and then manipulated using functional transformations such as map, flat map, filter, and so on. So your dataset API is available in Scala and Java, and Python did not support the dataset API, but I think that's been worked upon for the future releases. When we talk about data frame, it is basically a data set organized into named columns, or we can say representing your structured data or semi-structured data in the form of rows and columns, with columns having headings. So it is conceptually equivalent to a table in a relational database or a data frame in Python or R programming language, but it has richer optimizations under the hood. So data frames can be constructed from wide array of your sources, such as your structured data files, tables in Hive, external databases, or even existing RDDs. So again, your data frame API is available in Scala, Java, Python, and R programming, and your data frame is represented by a data set of rows. We can just say data frame is a simply alias of your data set of rows. Now, when we talk about your data frames, let's also understand about your Spark SQL data source API. Spark SQL, it supports operating on a variety of data sources through the data frame interface. It supports your different formats such as CSV, Hive, Avro, JSON, Parquet, text, and so on. As we know about in Spark, it is lazily evaluated like your Apache Spark transformations and can be accessed through SQL context and Hive context. So as we have seen in previous tutorials, your Spark context or your Hive context, or in later versions what we have is Spark session, these are basically the classes which are your entry point of your application. So when you start a Spark shell in an interactive way or a PySpark, you would see the Spark context is initialized, or your Spark session is automatically initialized. If you're building your applications using an IDE, then we would have to define and initialize our Spark context and Spark session, which is in later versions of Spark. In older versions, you had Spark context and then you had SQL context or Hive context. It can be Spark can be easily integrated with big data tools and frameworks via Spark core engine. Now, before we learn about Spark Catalyst Optimizer, let's have a quick look. So if I look in my machine here, and if I look in my machine, I could look in my C drive, and if you see here, I have downloaded Spark and Spark 2.4.3. Now, if you could follow previous tutorials, you would know how to set up Spark on Windows. However, just for new people, I can just give here some information saying, let's look at environment variables. And here I have set up two important variables. One is your Hadoop_home, which points to a folder called Hadoop on my desktop, and I'll show you what is there in that. I also have Spark_home, which has been set to my Spark path. Now, what does my desktop and my Hadoop folder contain? It basically contains a bin folder, and within that I have a winutils executable, which helps our Spark when launching to just realize if there was a dummy Hadoop support here. Now, what we can do here is I can go into my command line, I can go into my Spark directory, and then I can go in bin here. If I just do a dir/p, I would see that within this I have different binaries or different programs, and what we can do is we can just start by doing a Spark shell. So this is basically an interactive way of working with Spark. For people who would be more comfortable with Scala as a programming language, they could use Spark shell. Or if people are comfortable with Python, then they could be using PySpark. So here I'm trying to launch the Spark shell, which will run in a local mode. It will not be contacting any yarn or resource manager. However, it will just start an application locally on this machine. It will initiate the Spark context, as I mentioned earlier, or basically your Spark session, depending on which version of Spark we are working on. So if you see here, I have Spark version 2.4.3, Scala is 2.11. It has a Spark context which is available as SC and Spark session which is available as Spark. So this basically allows me to work either with RDD API using SC, or I could be creating a data frame using Spark. So both of these classes have got initialized and they will act as an entry point of my application into the cluster. In older versions of Spark, which is 1.6, we still had Spark context available. But then if we wanted to work on Spark SQL, which was launched in an experimental way with Spark 1.6, we could be using, instead of Spark session, we could be using SQL context or Hive context. So this is the Spark context or Spark session which is getting initialized. If I was building an application using IDE, then I would have to, depending on my use case and need, I will have to initialize Spark context or Spark session within my IDE. Coming back and understanding about your Catalyst optimizer. So when we talk about Catalyst optimizer, what is it? And what does it do? Spark, your Catalyst optimizer, leverages advanced programming language features such as Scala's pattern matching and Kasi quotes in a novel way to build an extensible query optimizer. So what it does, it works in 4 phases. Your Catalyst optimizer, it analyzes a logical plan to resolve the references when you are querying the data. It has a logical plan optimization internally, which will come up with the best way to get to the data. It has a physical planning layer, and then it also does code generation to compile parts of query to your Java bytecodes. When we talk about your Catalyst optimizer, we can say if you have a SQL query, now that SQL query would result in an unresolved logical plan, which can then help in analyzing the logical plan, and it also depends on the reference to internal catalog which has information about your data which you are trying to query. Then there is a logical plan based on the analysis and a logical optimized plan which is post your local logical optimization, which then relates in physical plans, and a cost model which helps the Catalyst optimizer know what is the best way to reach and access the data. It gives away a selected physical plan which will then generate code based on the RDDs which would be implemented based on your query. Now that's how Catalyst optimizer works. When we talk about SQL context or Spark session, as I explained, it is a class used for initializing the functionalities of Spark SQL. So in older versions of Spark, such as Spark 1.6, when you would start your Spark shell or when you would start your PySpark. So we can see that here. Now I could just do a simple quit, and I could then try bringing up PySpark, which is also a binary or a program to work with your Spark, but then that brings up your Python's shell, and useful for people who are well versed with Python as a programming language. Now if you see here, we again have Spark context initialized as SC, and then we have Spark session available as Spark. If I was working in older version, I would not have Spark session, but I would have SQL context, which could be used to use the functionality of Spark SQL, or basically using Spark to work with structured data. So your SQL context is a class which is used for initializing the functionalities of your Spark SQL, or you can say it is the class which becomes an entry point of your application for the resources which your application would need for processing. So we could just start a Spark shell, and basically that would start your Spark context or Spark. So when we talk about this Spark context or Spark session, you can also create a SQL context or a Spark session using something like this on an interactive cell. So you can say val SQL context equals new org Apache SQL context SC, and you could then start building your application. I will show that how you do that in your IDE, wherein you have to initialize your Spark context. However, as I said, in Spark Shell or in PySpark, your Spark context gets initialized automatically, and you can work with your RDD API, or you could be using Spark Session, which is available as Spark, to work on Spark SQL, whether you're working with PySpark or you're working with Spark SQL using your Spark Shell. Now, moving forward, when we talk about Spark Session, so this is an entry point to any functionality in Spark. So to create a basic Spark session, you could be using a Spark session.builder if you're working in an IDE like Eclipse. So here you have to import a package that is org Apache Spark SQL Spark session, and then you could create a variable such as val Spark. You could use Spark session.builder. You could provide an app name. You could also provide config properties, that is your configuration properties, and then you could say get or create. Now that creates Spark, which can then be used to work with your Spark SQL. You could then do import Spark implicits and continue to work. Now here, let me start my Eclipse parallelly and I can show you how it looks here. Now, when we talk about working with data frames, either we can be doing that using your Spark shell, PySpark, or we could be using our Eclipse. So let's see how we can work with data frames here. So let me just quit PySpark and let me get into Spark shell. So I could just do this, and this will start my Spark shell. That's an interactive way of working with my files. I could be using Spark here, and I could be using Spark session. Now for this, we would need some files. Now I could be working on Windows or I could be working on my Linux machines. So here I can show you both. Now this is basically a Spark standalone setup where I have set up things. You can refer to the previous tutorials where I have shown how you can set up Spark standalone or Spark on your Windows. I've started my Spark standalone cluster. If I look at the processes on these two machines, that would show me that I have a master and two worker processes. I can also open up the Spark UI if we would want to look into our applications. And here we can just say http://um1 and then 8080. So that shows me my Spark standalone cluster, which had two worker nodes. As of now, there are no applications which are started, and we can start Spark shell here. So I can go into user local Spark, and then I can see that I have basically a bin folder which has my programs or binaries which we can use. Now we could be using that from anywhere because in my bash RC, I have set up my Spark path. So that will allow me to give my Spark commands from anywhere. And here we can also see that I have some data in sample files. We can pick up one of the files here, which we can then use to create a data frame. So I can just say Spark shell from my home directory where I will target a JSON file, which is already here, to create a data frame. Now, once I'm starting my Spark shell, it basically shows that it has started an application. It shows a UI which is available. It is basically interacting with my Spark master. There is Spark context available as a SC and Spark session, which is available as Spark. Same thing we see in our Windows machine. That is, you have Spark context, a web UI available, which I can launch. I can look at Spark context available and Spark session, which is available. Now, taking this file, what we can do is we can say val x, and then I can say Spark which is the short form of Spark session. And then if you are not sure what method should be used, you can just do a tab and that will show you all the possible options which are available within Spark. So here we can use read and again do a dot and then do a tab, and it shows me that we can get our data in different formats. Now by default, if you do not mention a format, then it will expect the file which you are working on in a Parquet format. We can use a load method here, or I can just say spark.read.json and then I'll point it to a file which is in my sample files folder, and I will point it to people.json and I can hit on enter. Now here, since we are using Spark session, we will see if it creates a data frame. Now if you see here, it is pointing to a driver issue, basically saying it is not able to reach MySQL or the meta store. So by default, Spark also expects if it can connect to your meta store which is being used by Hive. So now I'm on my right machine, UM1, where I have my MySQL installed, which I just checked by testing, and I have my MySQL installed here, which is being pointed within the Spark conf by hive-site file. So now I will start my Spark shell again here, which should bring up your Spark context and also your Spark session. It will basically interact with Spark master, which is running on this machine, and as we have given in the conf and in your Spark default conf. So once my Spark shell has started, I can start doing this. I can say val x spark.read.json and then I'll point it to a file which is in this directory called people.json. So that's the file and it is in sample files directory. Now once we do this, we are using Spark session, which is available as Spark, and when I do this, it refers to the config files and then it is able to internally discover the Hive's metastore, which is in a MySQL database. That's because of the way I have set up my Spark standalone cluster, also so that it can work with Hive. Now here we see that a data frame has got created and we can always look into this. So I can just do a x.show to see what is in my data frame. So we pointed to a JSON file and my Spark session allowed me to create a data frame. Now at any point of time, unless and until you use a show or an action, you will not see the result. It would just create a data frame. Now here we have x.show, which shows my data frame. I can also do a x.print schema and then I can see what is the schema assigned to this. So in this way, we just easily created a data frame using a JSON file. Now if I come here and if I do a refresh, that will show me the application which is running, which has been started by Spark shell. I can click on this and then I can go into application detail UI to see what we have done. So I did a spark.read.json and I can look at the DAG here, which shows what happened, what code was generated, what were the transformations which were done. It shows me how many tasks were run for this. And then I can go and look back at my second job, which is basically ending with show, where I see this in a different stage. I see the code which was generated. I see the map partitions and then the map transformation. Also, we can always look at the SQL tab, which is getting created when you use Spark SQL. And within that, we can see what kind of queries were run, how much time did they take, and you can always click on the query to see what internally it did. So it's had a scan JSON, number of output rows, number of files, what was the metadata time, and basically I'm seeing the result. So this is how I create a simple data frame from a file. And as I mentioned, you can read any file format. However, if you do not give a format or if you do not specify the right method, then it will expect the file to be in Parquet format. So we just created a simple data frame from a file. Now we can do many other operations. We can do filtering, we can do selection. So we can do this. I can just do a x.select and I can choose one or multiple fields. So either you could use a dollar and then mention your column name here. Sometimes something like this. And then I could say I would want to look at the name, I would want to look at the age. But remember, if I just do this, it will just create a data frame. So if I would want to see the result, I will be doing a dot show, and that shows me what I have. I can always do some more things here. I can do a filter, and I can say I would want to see the age which is more than, say, 20. And at any point of time, when you do these transformations, it always creates a data frame or a data set. Now here I see that when I did a filter, it created a data set. So it is using the data set API. Now I can just do a show to see the result, and that will show me the result in the form of rows and columns with column headings. I could do a select, I could do a filter, and I could work on my data in this way on a particular data frame. Now you could also do some computations if you are interested in. So you could always do a x.select, and then you could be selecting a particular field. For example, I would say age, and I would say I would want to increase its value by 1, and I would like to do a show. So we are working on a data frame wherein it shows me the column name and then it shows me the values. So these are some simple data frame operations which we are doing based on a file which we have here. Now I could be picking up a bigger file and doing more functions or more transformations on that. I could be doing a filter, as I said, a select. I could be running my SQL queries by creating a temporary view out of it. Now here we could pick up a different file. I would say val my data, and then I could say spark dot read, and this time I'm going to use the format method here. So I'll say format. Now I would specify I would like to work on CSV file. Then I could basically also use something called as option, and then I could be specifying I would want to infer the schema from the file. So I'll say true. I will say option, and then I could also say a delimiter if you would want to specify. Now here I have infer schema as true, and we would then want header, that is first row in the file, to be considered as the header or the column headings. Then I can just say load, and I would want to load my file. So I'm going to pick up sample files, and then I will point it to a file which I think is existing in this directory, something like this. And then I do this, which should basically create a data frame from a CSV file. You see, it shows 15 fields and the schema is understood. So I can just say my data.print schema, and this will show me the schema which was inferred, and we have our data frame created. We can always do a my data.show, and that shows me some rows and columns. Now remember, it will always show you only 20 rows. If you would want more, then you could be giving it here in the bracket, and then you could see more values. So here we have created a data frame from a CSV file. We could do a filter, we could do a select from this, we could basically do any kind of computations. I could give different conditions. So this is a bank related data where some kind of campaign was done to find out if customers would be interested in subscribing for a deposit. Now all these sample files are existing in my GitHub link, and I'll share that link towards the end of session. You can always use these files, or you can use some of your own files. Now here I could just do a my data dot select, and I could be selecting multiple columns if I'm interested in. So I could just do a dollar. I could say I would be interested in age. I could be interested in job, marital status, or even the column which says about subscription, the last one which says why. So I could say dollar, and then I could say job. I would say I would want to see the subscription, and then I could be doing this, close the bracket. Now remember, that will just create a data frame. So we need to do a show to show me the results. So I'm doing a select, and I've started working on my data frame. You could be doing some other kind of calculations. Say we want to find out what are the total number of rows in this particular data frame. So I could just do a count, and then I could do show, or what I could do is I could convert this to a double value by doing this. and it shows me the total count of entries in this data frame is 45,211. Now I could basically be assigning this to a variable, say val total count, and then I get my value. So for example, we would want to find out what is the success rate of this campaign and how many people were really interested in subscribing for a deposit with bank. I could do that by just saying creating a variable called subscription count, and what I would want is I would want to work on my data frame. I would want to basically filter the values where the value for subscription holds true if it is yes, and then we could just do a count of this and convert this to double value like we did earlier for total count, and that tells me how many people were interested in subscription. So it gives me a count of people who were interested in subscribing for a deposit. Now we could do some computation on this. So we could say val success rate, and then I could just say subscription count divided by total count, and you could even multiply this by 100 to see the percentage. So it tells me the success rate of this campaign was 11% because this or these many number of people were interested in subscribing for a deposit. And in this way, you could be doing many more computations. You could be using different functions. You could be using different combination of functions. So for example, I could just do a my data dot select, and then I could say I would want the average on the balance column to find out what is the average balance of the customers which we would want to understand. Now here I could just do a show, and that could show me what is the average balance of a customer who was inquired about his or her interest in a deposit. In similar way, you could be using multiple functions like average, mean, median, percentile, and so on. Now there is one more thing about data frames. You could basically be creating a temporary view, and then people could be using their select queries to work on data. So we could do the same thing. Now here we could say my data dot create or replace temp view, and we could give it a name. So let's say bank data, and this basically facilitates querying. So now we can just use Spark.sql and then start using our queries to query structured data, which we would have basically used to create a data frame. So now I can do a select star from bank data where age is greater than might be 75, and I could just close this. And whenever I do this, remember, it creates a data frame. So if you would want to see the result, you can just do a show, and that will show you the result of your data frame. And we are seeing the fields which are having values greater than 80 or 75. So I not only created a temporary view, but now I am able to query that using Spark.sql. Now here, this is one way in which you can work with your data frames, work on different formats, look into the schema, run your queries, do some computations, and then basically also save it as a data frame. We could do many more things. So here, for example, if I would want to write this data in a different format or save it, I can always do a spark.sql. Now the same query which we ran here, we could put this in a variable. So for example, let's say val result, and I can just do this. Now I know that creates a data frame which has been now assigned to result, and now with result I can basically look into different methods which are available. So if you would want to save it, if you would want to write it in a particular format, remember, if you do not specify a format, then it will always be read or written in Parquet. So I can always do a write dot, either I could be using a particular format or I could straight away say save, and then I could say, for example, my new df data frame. And if I do this, the whole point is your data frame would now be saved on your machine in this particular directory in a Parquet format. So I can come in here and then I can look in if I have the directory created. So we see here and we can look in this. What does this have? And this basically has a Parquet file which got created. Now I can always do a SSH to my second machine because this is a standalone cluster, and then I can see if there was any directory created on this machine which has the data. If no, then that's fine. If we have a data directory, we can always look for our file. So we just saved the output of our data frame in a Parquet file, and that's my Parquet file. Now there is an easier way of checking if this was fine. So this is in my new df directory. Now what I can do here is I can just say spark.read, and this time I will not specify a format. And we know when we do not do that, it expects the file to be in a Parquet format. So I'll say load my new df, that's the directory. I'll give the file name, and then basically I'll see if it reads this Parquet file, creates a data frame, and yes, it has done that. We can always do a show, and we can see our new data frame. Now I know you might see some error like this, and that is because this file did not exist on both the machines. And when you're looking in a Spark standalone cluster, if you're trying to do a read operation, it basically expects the file to be existing on both the machines, or you should have been getting the file from a distributed file system. Now we can try this again, and I can just do a SCP. I can take this directory, and I know there is a SSH access which I have set up across machines. So I can say SDU at UM2 in the home directory, so that this directory and file exists on both the machines. And now we will try it again. So if you see, now I'm trying to read the file. I don't get any error message. So we worked on a CSV file. We created a data frame. Then we saved the data frame using write.save. And by default, it was stored in a Parquet format. We could test that by just doing a read.load. Now, the way we did a write.save and we did not give a format, we could have chosen a format. So we could have said format, and we could have said JSON, and then do a save and basically give a directory name. Now this is also saving my data frame, but now it is saving it in a format of my choice. So I can look in new df1. I should have my data coming in here. It might take some time, and then we can come back and check here if it has saved my file in a JSON format. So in this way, you can either store the data in a default format, or basically you can store it in a particular format of your choice, such as JSON or text or some other format. So this is how we are just interacting with a file on local file system. I'm creating a data frame out of it, and then basically I'm doing some computations. Now, as I said, if you have a setup, now in this case I have a Spark standalone cluster, but if I would want, I can start up a Hadoop cluster. I can just say sbin start dfs.sh. Now that will start my Hadoop related processes based on the setup I have. And why am I doing it? Because I would want to try Spark interacting with Hive. Now Hive is using HDFS as the storage layer. So I'm starting my Hadoop cluster. I can go into my second machine, and then basically I can again start my rest of processes. So I can just say sbin, and then I can say start yarn.sh, and that will start my yarn related processes. So I have a Hadoop cluster running, which basically means now I can also work with Hive. So I can just go into Hive directory. I've already set up Hive. I can get into Hive by just doing a bin/Hive. I can look into a database if it is existing. I can look into a table which is existing, see if that contains data, and try querying it using your Spark. So I can say show databases, and that basically shows me that I have a database called testdb. Let's use that in Hive. And now I'm in the database. I can say show tables. That shows me some tables. Let's select one of the table. I can say test DBL2. Might be we can just do a limit of 10 rows. and see if it works fine. So that does not have any data. Let's look into another table and let's see if that has some data. That also does not have any data, and that might be if we are not looking into the right metadata. Let's look into one more and see if that's fine. So we will say test tbl limit 10 doesn't have the data. So let's do one thing. Let's create a table. So I'll say create table new tbl. I will say id is integer, name is string. I will say the table is created. You can always do a listing from here by looking in user, Hive, warehouse, my test database, and then I can see if that my database has the table directory. It has new table. Let's look into that, new tbl. And then does that have any data? As of now, no. So I can say load data local in path. I will take this sample files. I know there is a file called kv1.txt which has internal format, and I will say overwrite into table, and then I can say new tbl. So I'm loading some data. It does not like because it does not find this directory. So let's give the right path. So we will say home hdu sample files. Now I'm loading some data. I've done that, and now I can say new tbl limit 10. So this is a simple example of loading some data in Hive table, which has two columns. We did not give any delimiters because I know the file also does not have any specific delimiters. Now here I can just exit this. Our main task was not to work with Hive, but to work with Spark SQL in interacting with Hive, which is a data warehouse package on top of Hadoop. So it is using Hadoop's distributed file system. Hive is using Hadoop's distributed file system to store the data, and we would want to use Spark SQL and especially its data frame API to work on interacting with Hive. Now let's do a spark.sql. Now if you remember, I mentioned that my spark conf directory has already a Hive-site file, so it knows where Hive is storing the metadata, and that basically means that your Spark SQL can directly work with Hive, and you can then start using all your Hive queries within Spark, benefit from in-memory processing and the data frame API. So here I can say use test DB. So I basically would want to get into the database, and I'm using this Spark SQL. You see there is an empty data frame created. Now let's say select star from new tbl limit 10, and I could do this, and this is basically your data frame. Now you could do a show, and you have started interacting with Hive directly, which creates a data frame which allows you to look at the data, and then you can store it in a variable. You can store this file. Not only this, you could also create a table from Spark SQL. So you could basically do all your Hive related operations from here using your data frame API. So I could be saying similarly create table new tbl2, and then I could say ID would be integer, name would be string, and then I could just close this. So I'm creating a table and I would like to close this. So let's do that. Now you see somewhere it interacts with Hive Metastore. It has created a new table, and that should be stored in my Hive Metastore and also on your HDFS where Hive related data is getting stored. Now we can even load data into it. So we will say spark.sql. I will use the same statement, load data local in path. I will pick up the file from sample files /kv1.txt. I will say overwrite into table new tbl2, close the bracket, and that should load data into your Hive table. Now let's try querying it. So we'll say spark.sql. I will say select star from new tbl2. I will say order by ID descending, and then I can say limit 10. So I'm running a query which, if would have run in Hive, would have triggered a MapReduce job. Now here, this uses a data frame, and you can always do a show, which will show you the result. So we are interacting with Hive, we are creating table, we are loading data into it, we are running a query using in-memory processing, using data frames, and that does not trigger a MapReduce job. If we had done the same thing using Hive, let me just show you here. So let's get into Hive. Let's start the Hive shell. Let's use our database, and then we can query our table. So I can do use test db, and if I say select star from new tbl2 order by id descending limit 10 and just run this, now you will see that this triggers a MapReduce job because Hive uses MapReduce. Now it also mentions on the first line that Hive on MapReduce is deprecated in Hive 2, will not be available in future versions. You can use other execution engines like Spark and Thais, but we are querying the table which we had created using Spark, and now we are using Hive to do it, which obviously takes more time. It triggers a MapReduce job and does the work for you. So this is how you can use your Spark SQL and your data frames to work. Let me just exit this. And there is one more option where you can be interacting with your RDBMS. Now that is, say I have MySQL here and I can log in into this. I can just say show databases. So I have my databases here. I can say use MySQL. I can say show tables, and then I can query one of the tables, like for example help underscore keyword, and then let's do a limit 10. So that shows me some data here. Now it would be good if we could interact with RDBMS and then get the data from here, and for that we will have to do certain things so that we can connect to this and we can work with this RDBMS. So if you look in your user local Spark, now that has a jars directory, and if I look in my jars directory, I have a lot of jar files here, but I would be interested in doing a grep and finding out if I have a MySQL related jar file. So if you see here, we have placed the MySQL jar file. Now where does this jar file come from? So this MySQL jar file, if I look in my home HDU downloads, and then if I look in here, you would see I have a MySQL connector tar file which I have downloaded. Now that particular tar contains your MySQL connector jar file, and this MySQL connector jar file has an inbuilt driver class which allows any particular service to connect with MySQL. So we need the JDBC connector jar file. Only then we can have our Spark connect with MySQL, which we already know is doing because your Spark is able to look at the Hive metastore, and Hive metastore is getting stored in MySQL. Now how do we establish a connection from Spark SQL to this MySQL? Like we connected using Spark Hive, you can always use Spark to connect to an external RDBMS, as I mentioned, and you can always search for that. You can just say Spark SQL JDBC data frame, and then look into the data frame documentation, which will show you the syntax. But for this, remember, you will have to set up a MySQL instance, you will have to get the driver, and then you can be giving all these options such as URL, DB, query, your driver, and then other options to connect to an RDBMS. You can connect to any particular RDBMS by just basically doing this spark.read.format, connect to an RDBMS, get the data from it, create a data frame, and work on it. For many more examples, you can always look into the data frame documentation. You can always be clicking on this, and then you can see how you can connect with Hive, how you can work with data sets and data frames. You can also look into different data formats which are selected, and you can do much more with data frames. Now here in this tutorial, we will learn about what is Spark MLlib, what is machine learning, about machine learning algorithms. You have Spark MLlib tools and different data types that it supports, machine learning pipelines, machine learning library algorithms, and then we can have a quick demo on Spark MLlib use case. Now, when we talk about Spark MLlib, of different components in Spark such as Spark Streaming, RDDs, your data frames or data sets, you have Spark MLlib, which stands for Machine Learning Library in Spark. The goal of this library is to make practical machine learning scalable and easy to implement. Now, when we talk about MLlib, this is Spark's machine learning library, and basically it provides tools such as ML algorithms, which include common learning algorithms such as classification, regression, clustering, and collaborative filtering. It also gives you featureization, that is feature extraction, transformation, dimensionality reduction, and selection. You have pipelines, that is tools for constructing, evaluating, and tuning ML pipelines. It has the features for persistence, that is saving and load algorithms, models, and pipelines. And then you also have utilities for your linear algebra, statistics, data handling, etc. So when you talk about your MLlib, it has a data frame based API, which is a primary API. Now, as of Spark 2 onwards, the RDD based API, that is in the Spark MLlib package, entered a maintenance mode. And your primary machine learning API for Spark now is data frame based API, that is spark.ml. We'll learn about that. Now, when you talk about machine learning and Spark's MLlib, it basically works on data which is collected. It can process the data, that is, you can build your machine learning algorithms using Spark MLlib. It also helps you in building data models, which can then be used for further processing. So before we understand about Spark MLlib and its features and its capabilities, it will be good to learn about what is machine learning. Now, machine learning is the science of training computers to learn from data and perform specific tasks without being explicitly programmed. And when I say training computers, it is basically training computers or making your algorithms learn by themselves based on the input which is provided. You have a lot of use cases for machine learning. Recently, I have been working in autonomous driving space, and again, there is a lot of usage of machine learning algorithms, especially in driver assistance systems, object classification, or even autonomous driving. You have various use cases where think about your mailbox, where you receive emails and they are automatically filtered and pushed into a spam folder. Now, how does that happen? So there is a machine learning algorithm running in the background which looks at the content of the data, probably looks at some words or patterns and identifies your mail as a spam. Take an example of Google search, where you would want to search something and your auto-complete feature allows you to complete what you would want to search for and then helps you in finding something. Other companies can be something like LinkedIn, where you have data-driven services based on the connections a particular user has, based on the postings a user has done. You could have recommendations based on courses or job openings and so on. And this is happening based on recommendation systems, which are also a form of machine learning algorithms. So when you talk about your machine learning, you have to have human intervention. So you would have data which might be accumulated. Now that might be batch data, that might be streaming data, and your algorithms or computer or system has to learn from the past data, and then it should be able to predict the output. Now when we talk about analytics, there are different kinds of analytics. So you have prescriptive analytics, descriptive analytics, you have statistical analytics, you have preemptive analytics, and you have predictive analytics. And in various scenarios, machine learning plays a very important role. It's an important branch of artificial intelligence. Now, when you talk about machine learning algorithms, they can be classified mainly into three main categories. You have supervised learning based algorithms, that is, algorithms which depend on labeled data or data which has response based on the features and which makes it easier to predict the output. Now, you might also have unsupervised learning algorithms that do not have labeled data or do not have responses. So they have unlabeled data and it is used to discover patterns from the data. You could also have reinforcement based algorithms, and in reinforcement learning algorithms, an agent receives a reward in the next time step to evaluate replicate its previous action. So these are three main categories of your machine learning algorithms. Now, if we would want to learn more on supervised learning, look at the image here which says label data of dogs and cats. And if this is the kind of data which is fed into your algorithm, we'd process the data, wherein it would again depend on the labels. So looking at the images, labels would say, well, the first part of the image is dogs, or you have cats, and so on. Now, once the data is processed, then you could say your algorithm is trained, or the model which is being used is trained based on the past data which was fed in, and then you have your trained model which basically can then look at an unknown piece of data to predict the outcome. So you could be working on label data, training your model, and then basically the same model can be tested against a data which does not have a label, but your algorithm would be able to successfully classify or identify the object. Now, when you talk about supervised learning, it is classified into regression and classification. So you have various different techniques. You have linear regression, you have logistic regression, you have decision tree, random forest, support vector machines, k-nearest neighbors, naive Bayes, and so on. So when you talk about these, one of the primary criteria of choosing supervised learning depends on the data what you have and whether that data has label or no. Plus it also depends on what is the kind of output which is expected. And based on that, one which is a data scientist or a developer would choose if he or she would go with linear regression or logistic regression, decision tree, or anything else. When you talk about unsupervised learning, now this is where your data is still fed to the algorithm, but here our data does not have a label or a response. Now, how does the algorithm work in that way? So algorithm would look at the features. Now, for example, if you look at the image, we might say feature would be color of the element or the size of the element or basically the shape of the element or anything else which can categorize or help us in identifying the object. So your unsupervised learning based algorithms would learn the patterns in the data, and based on that you would have your trained model which could then classify or group your objects into specific groups which have similar kind of characteristics. Now again, for your unsupervised learning, that can be classified into clustering and association rules. So you have various again techniques and models here such as k-means clustering, quite popular one. You have hierarchical clustering, you have DBS scan, you have principal component analysis, Gaussian mixture, and hidden Markov process. If you talk about reinforcement learning, so in reinforcement learning, it basically has to interpret the shape. Now, when we talk about reinforcement learning, as I said, an agent is provided a reward to identify a particular pattern. Then you could have your trained model, which basically would identify the element based on the shape or any other pattern. Now, for your reinforcement learning, the popular algorithms or techniques are your Q-learning, temporal learning, and your general adversarial networks. Now, when you talk about Spark MLlib tools, Spark MLlib component provides different tools. So when you talk about your ML algorithms, you have your classification, regression, clustering, and collaborative filtering. You also have for featureization, that is your feature extraction, transformation, dimensionality reduction, and selection. For your pipelines, you have tools for constructing and evaluating tuning or tuning your ML pipelines. For persistence, you have saving and loading algorithms, models, and pipelines. And then you have different utilities such as linear algebra, statistics, data handling, and so on. So when we talk about data types, so your Spark MLlib supports different data types. So it supports local vectors and matrices stored on a single machine as well as distributed matrices. Now for your Spark MLlib data types, as I said, it supports your local vectors and matrices. So it supports many data types, your machine learning library. Now you have local vectors and matrices which can be stored on a single machine, or you could have your distributed matrices which are backed by one or more RDDs. So your local vectors and local matrices are simple data models. they can be serving as public interfaces. Now you have certain tools like Breeze, which offers the underlying linear algebra operations. A training example which we use in supervised learning is what we call a labeled point in MLlib. Now when you talk about your data types, your categories could be local vector, it could be labeled point, it could be local matrix, and it could be distributed matrix. And then you have other criteria such as row matrix, indexed row matrix, coordinate matrix, and block matrix. So when you talk about your data types, now on the left we look at local vectors, where we are seeing a vector with certain values. You could have different formats supported here, that is dense format or sparse format. So if you would want to understand about vector data types, let's see this. So in your dense vector data types, a vector which is backed by a double array representing its entry values known as dense vector. So here we are looking at a double array representation. Now when you talk about your sparse format, this is a vector which is backed by two parallel arrays or two parallel array-like elements. So you have indices and values which are shown here in sparse vector. Now we could represent a vector such as seen on the first line 1.0, 0.0 and 3.0 in a dense format as a list of elements, or in a sparse format where we give the size of it by specifying 3, and then we give our elements, that is we are giving here 0, 2 and your 1.0 and 3.0. So here 3 is the size of the vector being the base class of your local vectors, and it provides two implementations such as your dense or sparse vector. Now we can basically create these dense vectors using Spark's MLlib package, that is linear algebra, which then supports your vector and your dense vectors for both the formats. We would have to import also some packages like Scala.collection immutable vector or MLlib.linearalgebra.vector. We'll talk about that later again in detail. When you talk about your labeled point data types, whether you're talking about dense or sparse, which is associated with a label or a response. So a labeled point is a local vector which could be of any of these types, such as dense and sparse, which is associated with a label or a response. So basically when we talk about your supervised learning algorithms, they use labeled points, right? Because supervised learning algorithms depend on labels. Now here we use a double to store a label. Therefore we can use label points in both regression as well as classification. Now a label could either be 0, that is negative, or 1, which is positive for binary classification. But if you have multi-class classification, labels should be class indices starting from 0, such as 0, 1, 2. And a labeled point is represented by your case class called labeled point. Now you have other data types also other than your local vector and labeled point. So you basically have local matrix. Now this has an integer type row and column indices and double type values that is stored in a single machine. Now here when we talk about your MLlib, MLlib supports dense matrices in which entry values are stored in a single double array in columns, as we see here with the major order. Now when you talk about non-zero entry values, they are stored in compressed sparse column format. Now if we talk about an example, let's look at this matrix what we are seeing here, which has 1.0, 2.0, 3.0, 4.0, 5 and 6. Now your one-dimensional array is represented in the form of matrix which has a size of 3 into 2. Here matrix or matrix is the base class of local matrix. It provides again two implementations. You can have a dense matrix and sparse matrix. And to create local matrices, we can use different factory methods implemented in matrices. Now when you talk about your distributed matrix, that has a long typed row and column indices and double typed values. So this is when you would have your distributed matrix stored distributively in one or more RDDs. is actually very important to choose the right format to store large and distributed matrices. So converting a distributed matrix to a different format can lead or can need a global shuffle, which is quite expensive. So there are 4 types of distributed matrices. So you have a row matrix in Spark MLlib, which is a row-oriented distributed matrix without having any meaningful row indices. You can say it is mainly dependent on RDD of its rows, where each row is like a local vector. When you talk about something like indexed row matrix, the difference with if you compare your indexed row matrix with just your row matrix is that you have some row indices here. So indexed row matrix is backed by an RDD of indexed rows in comparison to row matrix, which is RDD of rows. Now here the index is long typed and a local vector represents its every row. You could also have a coordinate matrix which is backed by RDD of its entries. So we can say each entry is a tuple here of, you can say, I as long, j as long, and value as double. So it's a row index where you could have a column index and the value. So these are your different types when it comes to your distributed matrix. You also have something called as block matrix, which we do not see here. But when you say block matrix, it is basically RDD of matrix blocks. Now, to understand matrix block, it is a tuple of int, matrix. So to understand these different data types, we can look at some examples and then it would be more clear in understanding different data types which your MLlib supports. When we talk about your MLlib basic statistics, now just looking at an example here, MLlib provides summary statistics for RDD, that is basically a vector, through the function callstats available in statistics packages. So we could be using, say, PySpark to work on MLlib. So you have pyspark.mllib.stat and you could import statistics. You could have your Spark context initialized. You could have your RDD of vectors. And then you could compute column summary statistics using your callstats on your RDD. So here we say summary equals statistics.callstats on mat, and then we could print the mean, variance, or num of non-zeros. So callstat returns the column-wise max, minimum, mean, variance, number of non-zero values, and the total count. Now this is just a simple example of using your MLlib and the statistics package. If you look further, and if we look at this example where we say MLlib can perform correlation between 2 series of data, again using your statistics package. Now in this example, we see we are using the PySpark MLlib stat where we import the statistics package. We would define our Spark context. We would then have our series. Now when we say series X and series Y, we are talking about 2 series on which we would want to perform correlation. So you have a series and the other series must have the same number of partitions and cardinality as your series X. Now you could be computing the correlation using Pearson's method. You could enter Spearman for Spearman's method, and if a method is not specified, Pearson's method will be used by default. So here we are saying print statistics.correlation, that is CORR, on these 2 series, and the method which we specify is Pearson. Then we have data, that's an RDD of vectors. So based on the type of input, if there are 2 RDDs which are of double type or an RDD of a vector type, the output would be a double or a correlation matrix. So this example just says that you could calculate the correlation matrix using Pearson's method, and you could also be using Spearman for using your Spearman method. When we say print statistics correlation, I could be saying I would want to work on a data which is a double RDD or an RDD of vector, and then I could be specifying my method. This is just a simple example of using Spark MLlib statistics basic package. Now, when you talk about simplifying methods, you have sample by key and sample by key exact that can be performed on RDDs of key value pairs or RDDs which have been converted as key value pairs. So your sample by key exact is not currently supported in Python, but in future the support might be added. Now this sample by key method or function will flip a coin to decide whether an observation will be sampled or not. You specify your Spark context, you specify the data, that is an RDD of any key value pairs, you give fractions, that is specify the exact fraction desired from each key as a dictionary, and then we use sample by key method saying data dot sample by key false and the fraction. So this is again one example, and we can look for these examples when we are looking into the demo of your MLlib. If you talk about your random data generation, then your random data generation is used for randomized algorithms, prototyping, and also performance testing. So if you would want to generate a random double RDD whose values follow the standard normal distribution of 0, 1 and then map it to a distribution of 1, 4, we could be using the random package here. So we say from PySpark.random import random RDDs. You create your Spark context. Now our aim would be to generate a random double RDD that contains 1 million IID values drawn from the standard normal distribution, evenly distributed in 10 partitions. So what we could do here is we could have your random RDDs dot uniform RDD, and here I specify my Spark context, I give the range, and then basically I say the number of partitions. So if you would want to apply a transformation to get a random double RDDs following the distribution of 1, 4, we could be using U, which is random RDDs.uniform RDD. You do a map and you use the lambda function to basically pass in the function which you would want to apply to get a double or a random double RDD with normal distribution of 1, 4. Now, when you talk about machine learning pipelines, now that is basically understanding your different stages, and that might include something like estimator, something which is evaluator, or you could also have your transformer. So machine learning pipelines provide a uniform set of high-level APIs, which is built on top of data frames, and it is usually and mainly used with your structured data or data which can be structurized. So it is used to create and tune practical machine learning pipelines. So as I said, when you talk about your pipelines, it would have basically your different stages. So when we talk about data frame, or in the older version of Spark, which was called as schema RDDs. So a data frame from Spark SQL is used as a machine learning data set. It holds a variety of data types such as text, feature, vectors, and labels. Now you also have something like a transformer algorithm, which is used to transform one data frame into another data frame. You have estimator, which gives you a model. So an estimator is an algorithm which can be applied or fit on a data frame to produce a transformer or to give you a model. And then basically you can have also an evaluator which will evaluate the model which was created. Now when we talk about pipeline overall, pipeline integrates your multiple transformers and estimators to specify a machine learning workflow. Now when we talk about your machine learning, there are two important pipeline components. You have transformer, which basically works on a data frame, transforms it to create one more data frame. When you talk about your estimator, you have a fit method which gives you a model, or you can say a transformer, which can be used for your further data processing. Now, before we understand about classification and regression in MLlib, we can just understand a little bit more on the classification and regression and what does that mean before we understand what are the different types for these two different type of algorithms. So when I talk about classification and regression in MLlib or in specifically machine learning and statistics, classification is a supervised learning approach in which your algorithm or computer program learns from the data input given to it and then uses this learning to classify new observation. Now this data set may simply be by class, like identifying whether the person is male or female, or that male is spam or non-spam, or it may be a multi-class too. So when you talk about different classification problems, you can have use cases such as speech recognition, handwriting recognition, biometric identification, document classification, and so on. When we talk about different types of classification algorithms in machine learning, then we have your linear classifiers such as logistic regression, you have naive-bayes classifier, you have nearest neighbor, you have support vector machines, decision trees, boosted trees, random forest, and neural networks. If we talk about regression in machine learning, then regression models are used to predict a continuous value. So predicting prices of a house given the features of house like size, price, etc. Or you could be having different other examples. So it's again a supervised technique. And when you talk about types of regression, you could have simple linear regression, you could have decision tree regression, random forest, you have support vector, you have isotonic, you have gradient boosted, and polynomial regression. Now, when you talk about regression, you could have your linear regression or you would have your logistic regression. In case of your logistic regression, this is used in different social and science applications. It is used when your dependent variable or target is categorical. Now, take an example. If you would want to predict an email is spam, then it could have an option as 1 or 0, which basically means whether the email is spam or it's not. Or take an example of checking if a tumor is malignant. And again, that could have binary values, which is 1 or 0. Or take an example of a content and you would like to classify it, whether that content is basically a science-based content or a social-based content. So in this case, you could be using logistic regression. Now, if we would have used linear regression for a problem like email is spam or not, there would be a need for setting up a threshold based on which classification can be done. Now, if actual class is malignant, predicted continuous value of 0.4 or threshold of value 5, right? Your data point would be classified as not malignant, which could lead to a serious consequence. Now, logistic regression can be very useful in solving such problems. If we talk about your binomial logistic regression, it is also referred as simply logistic regression, where it can predict the probability that an observation falls into one of two categories of a dichotomous dependent variable based on one or more independent variables that could be either continuous or categorical. Now, for this, I would suggest a little bit of reading on your dependent or independent variables, looking at your variate, univariate, multivariate variables, so that understanding on logistic regression can be in depth. Now, when we look at the example of binomial logistic regression, where we basically would want to work on a particular text file. So here we are using PySpark ML classification, and we are importing the logistic regression package. We would want to load the training data, and we would say specify a variable training. We say spark.read.format. We basically give a format and we load a text file. Now on that, what we would want to do is we want to use the binomial logistic regression. So here I say LR logistic regression, wherein you specify the maximum number of iterations, the parameters which you would want to pass, and elastic net parameters. You would want to fit the model. So you say LR model, and then you would want to do a lr.fit on the training data set. Now you could print the coefficients and intercepts for logistic regression using print and using string method str, and here you would be working on model.coefficients. We could also use multinomial family for binary classification. As shown here, you could fit the model on the training data set and finally print the coefficients and intercepts for logistic regression with multinomial family. When we talk about clustering in MLlib, then your MLlib supports following clustering algorithms such as your Gaussian mixture, latent Dirichlet allocation, bisecting k-means, and k-means clustering. So for k-means clustering, you could also be referring to, say, one of the easy examples of clustering, wherein this is basically an algorithm which allows you to cluster your data points based on some similarity. Now, if you look at this is just a visualization of k-means algorithm, where in your set of data points, you would select, say, random points, and then you would calculate the Euclidean distance or distance between different points with this random point. You would then shift the centroid in a cluster of points and again calculate the distance, and you would reiterate or iterate through this for a specific number of iterations till you can identify the right center point for set of cluster points which could be grouped together. So k-means clustering is a very efficient algorithm when you would want to cluster data points based on particular criteria. Have a look at this link for more details. Now here we also have an example of using k-means clustering. That is, you could be importing packages or modules such as NumPy, Math. Then you could be from your MLlib use clustering, wherein you would import k-means and k-means mode. You would load your file, and then you could be doing a map transformation where you would work on the values or the data coming in from this data.txt, and you could be performing a split based on delimiter or space. You would build the model using k-means.train method. You could evaluate clustering by computing within set sum of squared errors, and then you could save and load the model. Now we can see a demo on this, and then we could see how it works when you would create your applications using Spark ML or MLlib, and you could try and test those applications in a Windows-based setup or on a Spark cluster, or even where Spark works with Yarn. So let's have a quick demo on using Spark MLlib to solve some of our problems and see how Spark ML can be used. Now here I'll take an example of regression analysis. Now to understand regression analysis or regression line, it would be good to understand a little bit of basics about the equation of a straight line. And then we can see how regression analysis, which is a predictive modeling technique, which can be used to estimate the relationship between a dependent variable and an independent variable, which acts as a predictor. Now, to understand regression analysis, let's just have some quick basics. So for example, if you would have a line, say y equals mx plus c. Now this is usually a form of line, or you can say usually the equation of line. So a straight line is represented in this equation where you basically have m and c as constants. Now let's see how would that look like when you are basically having different points and you would like to have a line which can represent these different points in a particular graph. So for this equation, if we would want to understand, let's take a simple example. Say I would say y equals 2x plus c. Now if this is an equation and if we want to plot a line for this equation, we could consider, say for example, we could take a table which could have x and y values. So let's say x and y, and here we can just put in some values for x. So for example, I would start with -3, -2, you can have -1, you can have 0, and then you can have 1 and 2. Now if these are the values of x, and these values can be seen on this particular place where we would want to plot a line for this equation, and regression analysis relates to this, and that's why it would be good to understand the basics of the equation of line. Now here, if your x value is -3, and if we substitute that in this equation, so we would get the value of y. So for example, here it would be wherein you would say, let's say this equation is y equals 2x plus 1. Let's say this is the equation. So if I had value of x as -3, that would be 2 into 3 -6 plus 1. So that would be -5 for the value of y. Now you could similarly, if x value was -2, then it would be -4 plus 1, that becomes -3. And similarly, you could calculate, so wherein you will get values as 1 and then basically as 3 and as 4. Now, if we would want to point these values on the graph, then we could say for example, x, you have -1, -2, -3. So if this is my x for -3, and then y, I would go to -1, -2, -3, -4, and -5. So I could say my y point would be somewhere here, right? So that would be -3 being x and y being -5. Now, if we have x as -2 and y as -3, then I could say I would have my point here. If I would say x is -1 and y is -1, so it would be here. So if we already see these points are falling in a straight line. Now, if x is 0 and basically y is 1, so that would fall on the line itself. So we would put in here. Then basically we can have x value as 1 and y value as 3, so somewhere approximately here. And then you have the value of x value as 2 and then basically y value as 4, which would come somewhere here. So if I would join all these points, sorry for the curve, but then this would be a straight line. This would be a straight line. Similarly, we could take a different equation if we would want to see if this is a coincidence that we are getting a straight line for these points, or is there some kind of logic. So if I say y equals -x -3, and if I take a similar table where I would have the value of x and y, and x we can start with -4, -3, -2, -1, 0, and then 1. And if we calculate the values of y here, so if x is -4, then it becomes minus of -4, so that becomes +4, and 4 - 3, that gives me 1. So if you have x value as -3, so it becomes minus of -3, and then that becomes +3 and -3, so this would give me 0. And if we calculate further for all these values, we would get say -1, -2, -3, and -4. So this is the values what we have got for y and x. And if we would want to plot these values where x is -4 and y would be 1, so we could get our point here. If x would be -3 and then y would be 0, we would have a point here. If we have x as -2 and y as -1, so it would be here. Similarly, x as -2 we have done, and then we have -2 and -1. And then we could say, for example, if x value was -1, y value would be -2, and so on. If x is 0, y would be -3. So if we basically plot a line joining these points, approximately it would give me a straight line. Now here, this is how your equation of a straight line is following a form of y equals mx plus c, where your c and m are constant, and here we say m is a gradient, and I'll explain what is gradient, and your y is an intercept, and your c is a constant. Now if we look at these numbers and if we look at these lines, we can also see that whenever a value of x is increased by 1, so basically we have -3, and then you increase the value of x by 1, so that is -3, it goes to -2, so we would see the value of y increases by 2. Similarly, you increase the value of x to 1, so y value will increase by 2, and so on. So if we would want to look into the graph, so if the value of x was -3, and if we increase the value of x by 1, we would see the value of y would also increase by 2. So where my x was -3 and my y was say -5, now when I increase the value of x by 1, that is, I move towards the left, towards the right, my y value would also increase by 2. If you further increase the value of x by 1, you would again see the value of y value increases by 2, and that we can see on the line. So this is basically the equation of a straight line. Now if we compare that with the second equation, even there we would see the same pattern which would be followed. So when you increase the value or you decrease the value of x by -1, you would see the value of y would increase by y value would also be decreasing, right? So here if I say -4 has been increased by 1, so we would see the value of y is decreasing by 1, and then you again increase the value of x by 1, so you would see the value of y is increasing by 1. So if we understand these equations, then here we can see the value to what we see, the value of y which changes, or basically if you see the value of y here. So in first equation, whenever you increase the value of x by 1, it increased the value of y by 2. And that is what we see here, 2 in front of x. In the second equation, we see that whenever the value of x was increased by 1, your value of y was decreasing by 1, and that is what we see here. So these values, which is 2 or -1 in this case, are the gradients. Now at a particular time, your one of the point falls on the line of y-axis, and that is your intercept. So your y value is the intercept, your m is the gradient, and your c is the constant. Now this is what happens when we represent a line, whether the line goes in a positive direction or in a negative direction. Line is expressed in this form, which is y equals mx plus c, where m and c are constants. And if we look in graph, we see if the value of x is increased by 1 unit, then y value increases by 2 units. So this is how you can understand the equation of a line, which is represented in the form of an equation. Now sometimes you might also see that people would represent this equation as y equals b0 plus b1x, and that's also same as your y equals mx plus c, where your b0 is the constant, your b1, which is the gradient, is the slope of the line, and we could basically be representing this equation in any form. Now we could have basically x and y plotted on a graph. So if we had a small graph, we basically would want to find out if the value of x and if the value of y are related. That is, if you increase the value of x, does the value of y increase? If you increase the value of x, does your value of y decrease? So this is what we want to find out, and then we could basically get a line or a slope here. So you could either have a line going upwards or you would have a line going downwards. So this is how you understand the equation of a particular line. Now when we talk about real-time scenarios and when we talk about regression analysis, so if you have set of points which you need to work upon, if you have set of points, so basically finding a line that connects all the points possible is what you mean by regression analysis. So this line which connects all the points or all the possible points is called your regression line. Now this is calculated based on a least squares method, and we also need to minimize the estimated and actual value. So there are other points which do not fall on these lines, such as this or such as this, and these are called your residual points. Let's take a simple example to understand this. So for example, if I have x-axis, which is the height of a father, and y-axis is the son's height. Now we would want to find out if a change in father's height affects the son's height. So as we see the values of father's height plotted over x-axis, we could see or find out if that would basically relate to a son's height increasing or decreasing. So that could be represented in the form of your y equals mx plus c. Now if both of them increase, that is as the value of x is seen increasing, you see the value of y also increases, then that's a positive relationship. If the value of x increases but y decreases while x is increasing, now that is a negative relationship which would see a line going downwards. So your regression line or your regression analysis is about finding the relationship between dependent and independent variables. So let's look at this one. Now when you talk about your regression analysis, It's a predictive modeling technique. It estimates the relationship between a dependent variable, that is, in our case, we were saying whatever is on x-axis, and in an independent variable, which is on the y-axis. So x variable can increase its value as much as it wants. So far, an arbitrary value of x. We are predicting value of y. Now, prediction is done using regression. So when you talk about linear regression, we would basically want to find out a line that can basically connect all the points. Also, find out the points which would be your residual points, that is the points which are close to your regression line, whether your line goes upwards or it goes downwards. So your regression analysis is a supervised learning based powerful modeling technique, and it is basically used for predicting the unknown value of a dependent variable from the known value of an independent variable. Now, to look at a use case, what we can do is we can look at a data set here, and we can use Spark MLlib to see an example on that. Now, if we look at a data set here on my machine, which I have also uploaded in the Git link. So here you can look into this location where I have a sample data set which is called e-commerce customers. And if we would want to look into this data set, which is in a CSV format, let's look into this data set, and we can probably just look at some of the entries here. So we can say head might be -5. So this is the data set which I have, and it is in a CSV format where we see fields like email, address, avatar, average session length, time on app, time on website, length of membership, yearly amount spent. And then we have values for these. Now this is a CSV file. Now if we would want to find out what is the impact of yearly amount spent based on your fields, we would have to work on this data set. Now here we have some fields like email, address, avatar, and they would not have any kind of impact on yearly amount spent. So those fields are not required. But then we have other set of fields, which is basically your average session length, time on app, time on website, length of membership, and these fields are very important. So we could say your average session length, time on app, time on website, length of membership, all these are your independent variables. Your yearly amount spent is the dependent variable. Now, how do we do a regression analysis if we would want to work on this? So the first thing what we will have to do is, now as I explained earlier, your Spark MLlib has set of libraries and functions which can be used for your machine learning algorithms. So first, let's go to Spark, that is start Spark, and then import some packages. Now here in my machine, if we look in here, we have my Spark already set up. So let me see this. So here, if you see, I have a master and a worker running. And if I look at my second machine, I have a worker running. So I have a Spark standalone cluster, which has 2 worker nodes and 1 master, which we can also see from the UI. Now to test an application, first you can do the interactive way. And if that works, and everything is fine, you can even build an application using an IDE like Eclipse or IntelliJ. So here I see I have 2 worker nodes. I have my Spark standalone cluster running. So let's come in here and let's go back to this machine. Well, my Spark is already running, so I can just say Spark shell. Now there are other settings also which makes my Spark works with this standalone, but that's not the point here we are discussing. So we would like to do a regression analysis on this data set which has information about fields which can basically affect the dependent variable, which is yearly amount spent. As I was showing, we have average session length, time on app, time on website, and length of membership, which are the independent variables. So how do we work on this problem? So first thing is, let's import some packages which has these classes which will be used. So I will import one of these one by one, all of these packages. So import where we have your org, Apache Spark, and that gives me a error here because I had a typo, so this is fine. So I import the package which is going for ML evaluation regression evaluator. Similarly, I'll go for linear regression. That's what we want to do here. Then let's import some more packages, and we will go for log4j also. This would be good if you are building an application using an IDE, but we can just import the packages. Then we have a feature transformer, which is vector assembler. I'll show you the link where you can read more about it. And then we have vectors, because when you talk about machine learning, it would like to take the data as input in the form of vectors. So these are some of the packages which we have imported. Now, what we need to do is we need to get that data set which we can create a data frame from. So here the path for my data set is this one. So this is the data set I'm interested in. So let me take this one, which is e-commerce customers.csv. Let's come here, and what we want to do is we want to just paste it here. I will use it, and what we can do is we can basically create a data frame out of it using this statement. Let's copy this, and here let's go into our Spark shell. Now what I'll do is I have imported the relevant packages. So I will say this is my file. So I'll say file : home HDU, and that's the path where I have my CSV file which I just showed you. So what we are doing is we are doing a spark.read.option. We are using header as true because we want the first row of that data set to be considered as the headings. We have option as infer schema. We say format as CSV, and then we are loading the file. Now this should basically create a data frame out of this file, which we can easily use to work on the regression problem what we have here. So let's just wait till it creates a data frame. We can always assign that data frame to a different variable. So let's do that by doing this. So we know we have created a data frame here. It shows me in the last line, org Apache Spark SQL data frame. So now I will assign this data to e-commerce data frame. You can always do a ecom df.show to see what does your data frame contain, and it shows me the values which we had in CSV are now transformed and existing in the form of a data frame, where we have fields such as average session length, time on app, time on website, and length of membership, which are basically your independent variables. And you have yearly amount spent, which is dependent variable. Now, what do we do with this? So basically now we would want to look at the schema of this data frame to understand the data types. And we can do that by just doing a print schema, which tells me what are the fields, what are their types, which are assigned to them. So Spark has inferred the data type based on the values. Now, what we can do is we can filter the columns here, especially the columns such as your yearly amount spent, so that we would want to project as label, right? So when you talk about supervised learning, you would have always data which would have a label or a response. So your yearly amount spent would be a response or a label, and your other fields would be more or less like features. So let's get this, and here we can just do this, which says val ecom. So I'm creating a new data frame df1. I'm taking df which has been created earlier, ecom df. I'm doing a select, and I'm saying this yearly amount spent, which was the last column, would be the label. And then you have your other fields, which is your average session length, time on app, time on website, and length of membership. So I'm selecting all this data here, and I'm creating a new data frame out of it. So that's also done. You can anytime do a ecom df1.show to see what is happening in this data frame. Now, one point, as I said, your machine learning expects data in a n-dimensional vector format, that is a matrix format. It does not like the data in an array or a list or something, although vector is also like a list which is vertically arranged. So if you would want to read more about your ML features or a feature transformer like vector assembler, then you can basically refer to this link which I have given here. And if you just go to your browser and just search for this, you should be able to reach to the Spark documentation which shows about vector assembler. Now what is that? It's a transformer that combines a given list of columns into a single vector column. You see here, single vector column. It is useful for combining raw features and features generated by different feature transformers into a single feature vector. So we have multiple fields here, that is time on app, time on website, length of membership, and we would want to convert those features into one column. And that's why we are using vector assembler, which we have not used so far, but we would want to use it. So we created a new data frame. Now here, if you see, I am using new vector assembler, wherein I am providing the input columns as the array, that is average session length, time on app, time on website, length of membership, and then I'm saying set the output column as features. So let's copy this. Let's come here in my Spark shell. And what I'll do is I will use this vector assembler and I will say set input columns, which will then have these fields as features. So earlier we did yearly amount spent as label, and now we have this one, which will be your feature set. So now we have the data frame ecom df1. We have also the assembler, which should have the values in the form of a vector, wherein the heading of that would be features. Now we have done this. Let me just close this window. And now once we have used our vector assembler, we can basically create a new data frame based on assembler, which will transform your first data frame, which had labels, and then you are also using the features. So let's copy this, and I just want to avoid some time in typing all this and avoid any kind of manual errors. So here we are working on this assembler, which we created in the first step, and then we are doing a transform using the first one, and we are selecting label and features all together now. So this is done. It has created a vector. Now, if you would want, this is a vector. If you would want, and you would do something like this, it shows me the label and it shows me the features. Now, all the features are in one column, which is basically the three fields which we have combined together. Now, we have done so far. We can do a show. Now we can create an object of linear regression. So this is where we are then moving towards machine learning, where we want to use the linear regression here, an algorithm which is already existing. We just need to use it. So I'm creating an object with this linear regression. Then I can use the fit method on my data frame. That is what we created here, which is ecom df2. So I'm using a new variable called LR model. I will use this object of linear regression, and then I'll use the fit method. So I'm doing this, and this basically is implementing the least squares method. As I said, when you talk about your regression, which internally uses the least squares. So this is also done. Now we have the model, and basically what we can do is we can extract information such as coefficients and intercepts, etc. That is your gradient coefficients and so on. So we can just go in here and we can try in this. This basically gives me the coefficients and intercept, which will make obviously more meaning to the data scientists who are looking for the coefficient values and the intercept values. Now further, we can also look at the summary based on this model, and we can do that by doing this training summary. We have the model, right, which shows the linear regression training summary. That's what we have in training summary, and we can print out how many iterations were done or the total number of iterations, which should show me 1, and that's perfectly fine. And then I can also print the objective history training summary in the form of a list. So that's also done. And finally, we can also list down our residuals, that is the points which are not on the line, which are far from the line. And one of the main things as a part of linear regression is that you would want to reduce the distance as much as possible. So this is list of my residuals. So this is a simple example of using your linear regression, where we worked on a pretty much structured file, that is CSV, and this will give us information on your residuals, your gradients, your coefficients, and basically if we had a plotting integrated utility or software, we could have also seen this on a graph. So this is your linear regression and a simple demo on usage of MLlib. Further to this, if you would want to test or try this application, you can always refer to the GitHub link, where I have given the sample data set, the code, and also some more applications. So you can look into this path, which is the Git link with my name here. And here you can be looking into Spark applications and setup. You can look into the Spark MLlib folder where I have given you the sample dataset here, which is e-commerce customers, which I was using for this demonstration of using regression and linear regression. And you can also look into this linear regression document, which has the sample code, which we just now executed. Now for the application which we ran from an interactive shell, obviously we can go to the Spark UI, and here we can look for our application if we would want to look at the DAG and what it did. So here is my application. You can click on this. I can click on application detail UI, and which shows me that from the time we loaded data into data frame, wherein we created a data frame, what was the stage, what was the job number, we were doing a load, and it shows me what were the steps in the DAG. You can go further and you can look at all the show commands what you did, where you were trying to see what is there in the data frame, and even towards the end where you have show or you have count at linear regression or sum at linear regression metrics. So we can always see these steps. How many stages did it take? How many tasks were running? And basically DAG, which will give you more information on what happened on your application. You can always look at different stages. You can look at the storage if there was any caching done. You can look at environment variables, executors which were used for this particular application and the steps it had. And we can also look at the SQL tab, which basically shows up when you are using Spark SQL and data frames. And we can look at the queries which were completed. Always click on a particular link, and that can give you more details on what was happening in the background when you were executing a particular query or using a statistical model. So this is how you can run your linear regression using Spark ML, and you can build a model, you can build a machine learning algorithm which is following a supervised way of understanding from the data, separating the fields as features and labels, and finally helping us getting the slope of the line, getting the residuals, and basically also doing a linear regression on set of data points, which finally end up in giving up a regression line.
Let's have a quick demo on logistic regression and using Spark MLlib to solve a problem which is based on logistic regression. Now for that, let's also briefly discuss on what is logistic regression. Now this is a technique for traditional statistics and also goes well with machine learning, mainly to solve your classification problems. Now here outcome, that is the outcome variable or result, is binary. It could be 1 or 0, it could be true or false, it could be yes or no based on predictor variable. It's same as linear regression, but instead it predicts whether something is true or false instead of predicting something continuous like what we saw in linear regression. Now instead of fitting data into a straight line, it fits points into an S-shaped logistic function or an S-shaped curve. Now this S-shaped logistic function is called your sigmoid function. So you can search for sigmoid function in Google, and that could give you more information on how this function works. Now it also depends on a threshold value which we would set. Now below which we would basically have a probability of say 0, and above which we would have a probability of 1. So based on the threshold value which is set, we decide the output from this sigmoid function. So logistic regression is usually used for classification. It can work with continuous data or discrete data. Now here we test if a variable's effect on the prediction is significantly different than 0. If not, then variable is not helping the prediction. So logistic regression's ability to provide probabilities and classify new samples using continuous and discrete measurements makes it a popular machine learning method. Now with linear regression, as we saw, we fit the line for data points using a least squares method. That is, we find the line that minimizes the sum of squares of these residuals. Residuals are the points which are close to the straight line which we plot. Now logistic regression does not have concept of residuals. Instead, it uses something called as maximum likelihood, wherein through iterations the curve with the maximum likelihood is selected. So in case of logistic regression, we were seeing that when you have set of data points, you try to plot a graph or try to plot a straight line, which would be to have all the data points or maximum data points which would fall on that particular line. And that's how you find out the slope. In case of logistic regression, as I said, we would want to find out the probability of a result either being yes or no, or being true or false. So here the graph would look something like this. So it's a S-shaped curve where you would also have a threshold defined, and below which you could say that it would be, say, 0, and above which the data points would classify as 1, or below which the data points would classify as false, and above which they would classify as true. So that is the whole gist of your logistic regression. Now, how do we solve logistic regression? So MLlib also comes with different packages which can be used. So here we will try to solve a problem wherein the statement is you would want to predict a customer, if a customer would be bankrupt or no. Now this is probably for a bank which would want to identify if the customer is about to be bankrupt or no, and if customer will be able to pay back the loan. How do we do this? So for this there is a dataset qualitative bankruptcy text. Let me show you that. So here I have the dataset. Let me come out of this, and here we can look at the dataset which is in this location, and here I have qualitative bankruptcy.txt. This is the location, and if I look into this data set, it basically has some qualitative values which we will have to convert into quantitative. So if you look at these, this is the data set I have, which has P and N and A and B. Now we want to work on this kind of data set to basically classify the customer, if the customer is having more probability towards bankruptcy or no. How do we do that? So for that, what we can do is first we will start our Spark, when we will import some packages which are more for your logistic regression. So here I will start my Spark shell. Now Spark MLlib comes with different classes and different libraries which help us in solving these problems. So it already has these algorithms, say linear regression, logistic regression, and many more which can be used. So here what we will do is first we will import the relevant packages which are required for our example. So import. Now this is what we have. So Spark MLlib. So I'm missing in something here, and then we can get the others also. So there is a correction here which I'll update in the Git also. So it should be MLlib. Then we will get something else for the labeled points, and we will also get something for vectors, because when you talk about machine learning, it would expect the data in the vector format, for which in linear regression we saw using a feature transformer such as vector assembler. So these are the packages which we need. Now if you see here, I would want the data which we have to be understood. So the data file has these different fields, you can say, which are existing. So P is for positive, E is for average, N is negative, B is bankruptcy, or NB is non-bankruptcy. So this is the schema of the data file on which we have to work on. So what we would do is we would first transform each qualitative data in the data set into a double numeric value, which we can do using a function. So here we are defining a function called getDoubleValue. Let's do that. And this one will basically be declaring some variables, and then we would be converting the qualitative values into quantitative values. So that's the function. So let's copy this line by line, and looks like there was an error. Let me try it again here. So there was an error where there was an extra bracket, so I corrected that. So this is the function which will basically convert the qualitative values into quantitative values. Now once we have this, our function is ready. What we can do is further we would have to read the data in memory. Now here I would be using the older way, that is the RDD's way, to work on our data set. So I would be using val data sc.txt file, and then I'll point it to my file, which is qualitative bankruptcy. So let's get that file from here. So let me open up a different terminal, and here the file is in this particular location where we have this qualitative data set. So let's take this, is what we are interested in. So here I would say val, and then I would say basically data equals sc.text file. So using the text file method of Spark context, and here I would say file home htu, and that's my path of the file. So let's create an RDD of this particular file. Now once we have an RDD created, we can always see how much data we have here by just doing a data.count, and it shows me there are 258 rows which has these fields which we intend to convert into quantitative values using this function. Now once we are done with that, we need to prepare the data for logistic regression algorithm. So basically what we will do is we will do this where I will say parsed data. I will do a map transformation on my data wherein I want to split the data based on comma, and then I'm using the labeled point method wherein I'm using the function which we defined, which will basically then convert this data and convert the values into quantitative values. So let's do this, which says parse data, doing the map transformation, splitting the data based on comma as the delimiter, using your labeled point wherein I'm using the function, and then basically I'm going to convert that into a vector. Now once that is done, it has created an RDD which is based on MLlib regression labeled point, which we have used here. Once that is done, we can even print the data to see what are the values now, which should show me that my data, which was with attributes like P, A, etc., has now been converted into the quantitative values which we can use for any kind of computation. Now once this is done, then you can split your data into training and test data set, which will be used to train our algorithm. So what we will do is we would do splits wherein we are converting this into a 60 and 40%. So let's do this. Once that is done, I could then have my training data, which will be at index position 0, and I will have my test data set, which will have at index position 1. Once this is done, then we need to train the model. So how do we train the model? Now this is where we use the logistic regression algorithm with LBFGS. We will take this and we will apply this on our training data. Now once this is done, we have a model which is based on logistic regression, which would work on our training data, which is 60% of our data set. Now once this is done, it has basically given me a model, logistic regression based model. Now here I need to evaluate the model on training examples and compute the training error. So I can take this wherein I am working on test data. So that is being applied a map transformation where we would want to see if my model is working fine. So let's get this here, and that's done fine. So our model looks fine. Now we can basically get the training errors based on this. And once this is done, you can print your training error out of what you have done in the previous step. So that gives me training error of 0.20, that is 20% is the error. Now this is a simple example of logistic regression where we are basically reading data in memory. We are preparing the data to be used by logistic regression algorithm. We are then splitting our data into training and test. We are training our model, and then we are evaluating our model on training examples and computing the training error. So this easily shows how we can use Spark MLlib to basically work on your problems such as linear regression or logistic regression. Now since we have run the application, we can always come back here and we can look at our application which was launched using Spark Shell. We can look at application detail UI, which will show me what are the different steps we did when we were using Spark MLlib, and you can go into any one of these jobs and see what it has done. You can look at the DAG of the steps which were executed, which shows how we picked up the file, what kind of transformations we did, and finally how we got our resultant data. Now here, this is my Spark UI. If you would want to look at the code and the sample dataset, you can find on the GitHub link in this particular place where you have Spark MLlib, where I've given you the documentation with the code. I've also given you the sample document, which sample data which can be used, and a notepad file which also has the code wherein there is one correction in our function which can be changed.
Here we will learn about what is PySpark, what are PySpark features, PySpark with Python and Scala, PySpark contents, PySpark subpackages, companies using PySpark, and also we will see some demos using PySpark. So what is PySpark? Now, it is in Python's API to support Apache Spark. Now, all of you would have known about Apache Spark or would be knowing a little bit about Apache Spark as of now, that is a in-memory computing framework which basically gives you a faster processing capability, and it is widely used in terms of real-time processing or machine learning, and then there are various other use cases. So when we talk about Apache Spark, it supports different programming languages such as Python, Scala, R, and even you could be working on structured data structures using Spark SQL. Now we all know that Spark context is the entry point to any Spark functionality. So we'll see that. Now here, when we talk about PySpark, it is basically a way of using Python, or for people who are more comfortable with Python programming language, to use Python and work with Apache Spark. And that's what you have as a component from Spark called PySpark. Now here, just to show you, I have two machines. Now I have already set up a Spark standalone cluster on these two machines. So if you see here, I've given a start all command, and this has basically started my Spark master and two worker nodes. So we can check this by just doing a JPS on this machine. And if I go to my second machine and if I do a JPS to see the Java related processes, I see two workers and a master node running. So my Spark as a standalone cluster is running. Now we can always check this using the Spark UI. If I go to my browser, and then if I just do http / and then if I say um1 and 8080, so that shows me my Spark cluster, which has two worker nodes. It shows their address and all these details. Now, if we come back to the terminal and if I look in binaries, so I see a lot of Spark related programs, like you have Spark Shell. If you would be interactively working using Scala and you would want to work with Spark, you can use Spark R if this has been set up, and you can use your R programming language knowledge. You can be using Spark SQL to work with structured data. You can use PySpark, which is Python's API, allowing users to use Python to work with Spark. And obviously you also have Spark Submit. Now the other way would be that if your machine has Python installed, you could write your applications in a Python file, that is a file with an extension of .py, and then you could be using that. So here, if I would want to work with PySpark, I can just say bin PySpark, and that should start my interactive shell in Python. And then basically I can be using my Python's language. Now here, if you see, it says Spark session is available as Spark, and then by default when you start your Spark shell or basically PySpark, it would have Spark context, which is the entry point of your application available, so that you could do your processing. Now there are different ways of doing it. For example, if I would just say xsc.text file. Now text file is basically a method of Spark context, and as I said, when we use an interactive way of working with Spark, such as using PySpark or Spark Shell, then we have Spark context and Spark session automatically getting initialized. If we are building our own application using an IDE, for example in case of Python using a PyCharm, or you writing your code in .py files, then in that case you would have to initialize the Spark context. Now here I could be pointing to a particular file which could be coming in from my machine. So for example, I could do this home/stu /sample files, slash, let's take a file which I think should be existing here in this location, and this file and this directory would be existing on all your worker nodes. So if I just do this, we know that this, since we are using Spark context, which is an entry point, it would have created an RDD. Now RDDs are the building blocks of Spark. You might have learned about that through the previous tutorials. Now if I just say what is X, it shows me it is a map partitions RDD which has got created because we used a Spark context. Now if we do further transformations on this RDD, it will further create multiple RDDs. So we'll see that, but this was a quick look at you using your PySpark. Now we have not seen the complete execution, but if I go here, if I say refresh my UI, it tells me that there is an application running. So we have started the PySpark shell, which is using all the cores of the machine. It is basically using 1 GB memory. And then we have an application which was started because we started PySpark shell. Now I'm clicking on this. I can go to application detail UI, and as of now, I have not done any execution. In terms of Spark, until and unless you invoke an action, everything would be lazily evaluated. So we don't see anything here, but we do see that PySpark shell has started an application. That application is using some resources, and basically as we do further processing, we will see the application related DAG getting built up. Now, when we talk about PySpark, as I said, it's Python's API. Now, if we look further into PySpark features, it basically, as I said, when you work with Spark, it is a in-memory cluster computing framework, which is polyglot, which basically supports different programming languages, such as you could be doing things with Scala, you could be doing things with Python, you could be working with R, or you could also be using Spark SQL. When we talk about other features, Spark also allows you to do faster processing. It allows you to do real-time analysis, and there are also features where you can be caching in your computation. That is the intermittent computation. So you could be caching in, and you could also have disk persistence. So those are the features of your Spark, and when you work with Python, you will be able to leverage all Spark's features. Now, when we talk about Spark with Python and Scala, and if we do a quick comparison, if we talk about performance, then Python is slower than Scala when used with Spark. However, when you talk about Spark, since it is written in Scala, it integrates well and it is faster than Python. Now, learning curve. Obviously, we know that both of these languages support concise code, and Python is very rich with the amount of libraries which are available, community support, and so on. But Python has simple syntax, and being a high-level language, it's easy to learn. Scala has a little bit of complex syntax since it is newer in comparison to Python, but then it also allows you to write concise code. And sometimes it might be for the new programmers, learning Scala might not be so easy in comparison to Python. When we talk about code readability, so in case of Python, readability, maintenance, and familiarity of code is better in Python API. Now, Scala is a sophisticated language. Developers have to pay a lot of attention towards the readability of code. And if we talk about data science libraries, as I already mentioned, Python provides a rich set of libraries for data visualization and model building. Now, Scala lacks in providing data science libraries and tools for data visualization. There is a lot of work happening when it comes to data science and machine learning with Spark, different components such as MLlib and ML, which allows you to work with data science kind of projects. However, Python would be more advanced in that case. Now, when we talk about PySpark contents, so these are a quick list of PySpark content. So you have a Spark conf. Now that is basically how we define our configuration. So we would be creating a configuration object using Spark's Spark conf class. Spark context is basically the entry point of your application, which will basically take your application to the cluster manager, whether that is Yarn or it is Spark master in case of Spark standalone, or even local. Now we have Spark files. Now that allows you to read files from a file system, whether that's a local file system or a distributed file system. You have RDD. These are the building blocks of Spark. That is, anything you do starting from using a Spark context or Spark session till you invoke an action. That is, anytime you use a method of Spark context or Spark session, you do some transformation, you are always creating an RDD. That's a resilient distributed data set in memory, and that is in one way a logical step which is part of a DAG, that is direct acyclic graph, which gets executed when you invoke an action. Now you also have storage level and different classes within that, which allows you persistence. You can be using Spark's higher API such as data frame or datasets, and then you also have ways where you can be efficiently doing wider transformations or wider operations using broadcast and accumulators. Now, when we talk about Spark Conf provides configurations to run a Spark application. Now, we will see that further when we build our applications using PySpark. Now, if we look at the code block of Spark Conf class, which is used, so that would show you class PySpark.SparkConf, and that has load defaults. It has for JVM and J configuration, which can be passed. Now, if we look further, these are some of the most commonly used attributes of Spark Conf. So you have something called a set key and value to set a configuration property. And this is where we can be passing in our configuration properties and passing in values. We can basically say how many executors we would want for our application. We can say how much memory per executor or cores per executor, and many other properties which can be set in the form of key value. Now you can also be saying set master and then pass in a value. Now that will take your master's URL. You can set an app name, which is basically value to set an application name, and you can do a get key and default value to get a configuration value of a particular key. Now there are various other options which you can use with your PySpark.SparkConf. So if we look into Spark context, now as I said, when we understand Spark architecture, which you would have learned from previous tutorials or some of your ways of self-learning, that's Spark basically has, or whenever you build applications to work with Spark as a processing framework, your applications would have a driver program, and driver program basically has a Spark context. Now Spark context is the main entry point in any Spark program. So if we look at the data flow, so in terms of local, we are talking about Spark context, which basically allows you to talk to local file system. And then you basically have something called as Py4j. So when you run any Spark application, a driver program starts, which has the main function, and it has your Spark context, which gets initiated. Now the driver program then runs the operations inside the executors. So what are executors? These are JVM processes. Now Spark context uses Py4j to launch a JVM and creates a Java Spark context. By default, your PySpark has a Spark context available, which I just now showed on the machine, and that's your SC. So creating a new Spark context would not be required if you are working in an interactive way. But if you are developing your application using an IDE or basically in a file, then you would have to initialize your Spark context. Now, if we look here, so we see that Spark context has some kind of socket connection with Spark Py4j implementation, that's the JVM, and then you could be having a cluster underlying which has multiple worker nodes, wherein on those worker nodes you would have executor processes which will take care of your execution. Now, if we look at this code, we see that this is an implementation of PySpark class and the parameters Spark context can take. So we can be passing in values for all these parameters such as master, app name, Spark home, Py files, and so on. So master, now this is where you will say the URL of the cluster it connects to, right? So we would be interested in using Python to work with Spark, and Spark would be either as a standalone cluster or that would be integrated with Hadoop or Apache Mesos and so on. So your master will point the URL of the cluster. App name is basically your application name. Spark home basically says where your Spark related jars or config files or what's your Spark installation directory. Py files basically tells the .zip or .py files to send to the cluster and add to the Python path. So this is where you would specify what are the Python files wherein you have written the code which needs to be added to the class path. You have a parameter environment wherein you would specify worker node environment variables such as your JVM or your memory and cores which need to be used. You have something called as batch size. So this is number of Python objects represented as a single Java object. Now it is set 1 to disable batching, 0 to automatically choose the batch size based on object sizes, or -1 to use an unlimited batch size. Then you can also be specifying serializer, and this is the serializer which will be used. So RTD serializer, now here we can be specifying, say for example, pickle serializer. So by default, we know that when we work with Spark and we work with RTDs, Spark internally uses either a Cairo serializer or Java serializer. You have something called as conf. Now this is an object of your Spark conf to set all your Spark properties, right? So this is where we are creating a configuration object. We have something called as gateway. Now we can use an existing gateway and JVM, otherwise initialize a new JVM. You have Java Spark context instance, that is JSC, and you have profiler. Now this is a class of custom profiler used to do profiling. And for example, we can pass in pyspark.profiler.batch profiler. So in all these above parameters, master and app name are mainly used. Now we could basically write a particular code, and I'll show that in further slides, wherein we can just say from PySpark import Spark context, and then we can be specifying parameters which go into the Spark context. If we go further, we can see how that looks. So Spark files. Now, what is this used for? So you have Spark files, which allows you to upload your files using methods of Spark context, such as add file. And you can even get the path on a worker node using Spark files.get. So this is just a simple example which we can use. So you have these class methods. One is get. So you can get the file name, and you can even say get root directory if you would want to look at the path. So this is a simple example. Now get root directory function here, or method here, specifies the path to the root directory, which basically contains the file that is added through your add file method. So if I would be writing the code in a file and not doing it interactively, I could be doing from PySpark import Spark context, from PySpark import Spark file. So if we are doing it from the interactive way, we don't need to really use Spark context. We can just import Spark files, and that should be enough. Then here I'm saying find distance, and I'm specifying a path to a file. Then basically I am saying find distance name, and then I'm pointing to this file. Here I'm creating my Spark context, or I'm initializing my Spark context by passing in parameters such as what would be my master, and I'm saying local, what will be my app name, and I'm saying Spark file app. And then I'm using a add file method where I'm passing in this find distance, where we have created a variable to point to a file. Finally, I'm doing a print absolute path, and I can also say Spark files.get to get the root directory for this particular file. So we can be just doing this in a simple way, and I'll show you some examples here. So when we talk about your PySpark RDD, now RDD is the building block of Spark. So you have resilient distributed dataset. That is basically the basic abstraction in Spark. So anything you do in Spark until you would want to see the result, starting from using your sc dot method till you're doing transformations like map, flat map, filter, or any other transformations, all that would be creating a resilient distributed data set. And what is that? It is basically a logical data set. When data is not evaluated, you're not doing any transformation, every step in your application is ending up creating a RDD. And that RDD is basically a step in the DAG, and this DAG will get executed when you invoke an action. So it's an immutable partitioned collection of elements. Now by default, whenever an RDD is created, it will always have partitions. and we can always look at the partitions. We can see how many partitions are there, and the more number of partitions you have, the more number of parallel tasks you will have. So when we talk about RDD, there are mainly two kind of operations. So you have transformations. So these are operations such as map, filter, join, union, and so on, which are performed on an RDD that basically results in a new RDD. Now, how is the first RDD created on which you could do a map or a filter or a join or something else? Is by using a method of Spark context. Like I showed you an example in this session in the beginning. Action is when you would want to see the result. So these are operations such as reduce, first, count, take, and so on, which basically trigger the execution of DAG right from the beginning. So this is a simple example of creating a PySpark RDD. So here you are using class PySpark.rdd, and then you are saying JRDD. You can have your whatever name you would want to give, like context. You can be specifying your serializer which you would want to use. Okay, so if I would be doing this in a file, I would be writing in code like this. Now this is just a simple PySpark program to return the number of elements in the RDD. So you are creating a Spark context. You say sc.parallelize. Now sc.parallelize is a method to work on collection of elements. And here you have some words which are being passed. So this is just like a collection or a list, you can say. And then you are doing a counts where you take this RDD and you are just doing an action on it. Now that would give you the result, and finally you are printing it out. Let's just have a look at some examples where we can use PySpark and in an interactive way. So let me go to my console here, and what I can do is, for example, I can be referring to a file. Now, as I said, with your Spark context and Spark session both get initialized. So here we can use SC, and then with SC you have different methods which can be used to work with your Spark. Now here we can be looking at method like text file, which basically allows you to pick up a file. So let's say text file, and then I can be pointing it to a path. So I can say home HDU sample files. Now that's a directory in my machine, and this directory exists on both the worker nodes because we are working on a Spark standalone cluster. And here, for example, I can pick up people.txt. So I know that there is a file here in this path, and let's also give this in quotes. So this would have created a RDD. If I just do X, it shows me that it has created a map partitions RDD using a text file method. Now I can do some more transformations on it. So for example, I can say y x.map, and map is basically a transformation which I'm doing on an RDD which is already created using a method of Spark context. So here, when I would want to do a map, I would have to pass in a function. Now in Spark, and when you're using Python, you can be using lambda functions, which is for anonymous functions. So I can say lambda, and then I can say take every element here, and what do you want to do with that? So I can say n.upper. Now that's a inbuilt function which we can be using, and when I do this, this one would again create an RDD, and here we see it has created a Python RDD, and this RDD again has not really done the evaluation. Now unless and until we would want to look at the result, there is no evaluation happening here. So in the first one we created an RDD using a file. In second one we applied a function using map. Now I could do a filter, I could just do a simple y.collect, and that's basically an action which you are invoking, which will let this DAG get executed, and then I look at the content of my file which has been converted into an uppercase. This is one example. Now I could also be, say, creating a list. For example, let's create a list of strings. So let's say hello, let's say world, let's say cool, let's say winter, okay, and let's say summer, So I could be giving in some words, and this usually creates a list, right? So I've created a list and I can basically see what is this. So it has created a tuple, and that's also fine. So basically now you have created a list or a tuple and you would want to work on it. So it's a collection of elements. Now I can basically say B, and then I can use again sc dot, and this time I would be interested in using this method, which is parallelize, which allows you to work on collection of elements. So I can just pass in A here, and if I look at B, it has basically created a parallel collection RDD using the parallelize method of Spark context. Now we can be printing out some values from here. So for example, I could also be invoking an action. So I can say b.count, and this should give me the count of elements in this particular RDD. So these are two applications which I just ran, starting from creating a list, passing it in parallelize, and then doing a count. Or in our previous example, we read a file, we applied a map function, and then basically we did a collect. So if I would go back to my Spark UI, if I would do a refresh, now here it shows me the application which is now running. You can look at application detail UI, and that shows me the two jobs which have run, starting from the first RDD created till the action was invoked. So if you look at this one, so this one shows me the DAG, and it shows me it started with a text file, and then basically you did a map. So it also shows me how many tasks which were run. So this also means that there were two partitions created for this particular file. And I can also be looking at, say, different stages, what were there in my application, which has two jobs. You can look at storage if there was any caching done. You can look at the environment variables. You can look at how many executors were used for this particular application, and how much memory was used for storage, how much was it for processing, if there was any shuffling happening. And you can also look at a Spark SQL, although we are not using any Spark SQL component here. If I look at the second one, which shows me 4 tasks, so it started with parallelize, and then basically we created a Python RDD. We finally ended up with a count, and this tells me how many tasks we had run. So we can always go and look at the number of partitions of a particular RDD. So whenever you would be creating an RDD, so for example, we have B here, or in this case, we have Y here. So you can always do a Y dot and search for different methods which are available, and then you can basically be checking. So for example, if I would want to look at the number of partitions, what was created for these Y when I was converting my text into uppercase, and then I can be just doing this, and this will tell me how many partitions were created. Similarly, if you would search for B, which was when we worked on a list, and if you would want to see, so it shows me the number of partitions were 4. And that also tells me that based on the number of partitions, you are seeing the number of tasks which were executed. So automatically, based on your data size or based on the number of cores which are being used, it has created partitions, and per partition you would have a task running, right? So for example, we had this where we were creating a list, and then in B is what I was doing was I was doing sc.parallelize. Now what if I had done something like this? So if I would have done something like this, then my B would have created 2 partitions, right? And then if I do a execution on B, like what we did for count, so it still gives me the count, but now the partitions were 2. So we can again see how many tasks were run. So if I go back here, and if I go to the jobs, and then I see one more job which was run, and you see it shows me 2 tasks. So the same job which was showing 4 tasks earlier is showing now 2 tasks, and that basically means that the number of partitions was changed, and per partition you will have a task running. So this is just a simple example of seeing how you can be basically using PySpark. Now I could also be taking this whole thing and putting it in a file and then executing it, and I'll show that later. So when you talk about storage level, now that's a very important concept. And if you have followed previous tutorials where we would have spoken about storage level, so basically this decides whether the RDD should be stored in memory or should it be stored on disk or both. So when we talk about your storage level, now if we look into the package which comes for Spark, it basically has storage level, and you can always go to Google and check more for this one. So for example, I could basically be checking this. So for example, if I would say storage level and just check this, so storage level, and then you can do a Spark. And you see, it says you have different options, memory and disk. You have memory only serialized, memory and disk serialized, disk only, memory only. So there are different options here. And this one, you can also search what package it comes in for. And then you can see there should be a package which talks about storage level. And that would be, for example, let's see. So here it says org Apache Spark.storage level. Now this is a way wherein you would be importing a package in terms of Scala when you're doing, but then storage level as a class comes within your org Apache Spark storage level. And similarly, you would have your storage level for PySpark also, wherein you have to import the particular package, and this storage level then has different options like memory only, disk only, memory and disk serialized, and so on. So here what we can do is we can basically see what is the usage of storage level. So in this example, if you see, we are saying class PySpark.storage level. Now we could be saying it should use disk, or it should use memory, it should use off heap, or should it be deserialized, what should be the replication. So storage level is one way wherein you can have your RDD which gets created at any step of your application to be cached. So that's basically making your computation cached or computation persisted, so that if down your application, if you are using the same step again on same series of step, you will not have to have your complete DAG executed right from the beginning, but you could benefit from the cached or persisted computed RDD. Now here we are saying from PySpark import Spark context, we are saying import PySpark, and here we are creating a Spark context, that is Spark context local storage level. Then I say I would want to do a sc.parallelize on these elements, and then I can basically say that this RDD which gets created in this step needs to be persisted using PySpark in storage level, and then you can say memory and disk with a replication of 2. Now I could then just be checking if my RDD was persisted, and I can check for the get storage level. I could even print it. So this basically tells me that if I was doing something on RDD1 for the first time, it would have cached my computation or whatever we did in this step in one of these options which comes as a part of storage level. And if next time I would be executing that series of step, it would benefit from getting the data from cache. Now here we have a quick example of using storage level and then caching your RDD, and we can then also see how we can recognize if that is coming from your UI. The information can be seen in UI, and you can see if the caching is really benefiting. So for example, like what we did earlier, we can basically create a list, and then I am doing a b sc.parallelize. And here, before we can use this PySpark, we will have to import the package. So for example, I could be just doing this. Now I could import this PySpark package here, which we will be using to use the storage level class. Now what we were doing earlier is we were just doing a b.sc.parallelize. Now that creates an RDD, and we can do that. And here I am doing a persist, where I'm saying that sc.parallelize, which creates an RDD, that RDD or that stage of computation should be persisted using PySpark storage level, and I'm specifying memory only. And as I said, you can have different options here like memory only, memory and disk only, memory and disk replicated. So you can give different options here with storage level. Now we could be straight away doing this, where we will be caching in this in memory. Now once I've done this, I can basically just do a b.count, and when I do this, now this b.count would have triggered the execution of DAG right from B onwards. So basically this list would have been created. That's not part of your DAG. Here I'm basically using sc.parallelize. So this is where my first RDD is created. You're persisting it and then you're doing a count. Now if I go back to my UI right now, if I do a refresh, it basically shows me an application which completed with 2 tasks. If we see here, we see that there was a parallel collection cached, now which we have done that, and it shows the duration is 2 seconds. If I look at my storage, it shows me that the parallel collection was 100% cached and the size in memory is 175 bytes. And then it says how many partitions were cached, and we can look at the executors to just tell me we had one for driver and then you had 2 executors for 2 tasks. Each one of them were running on 2 different nodes. They were using by default 2 cores. How much memory was used for storage, how much was used for execution. It tells how many tasks were run by each executor, and that gives me an overall summary. Now if we basically run this again, now what will this benefit from? We will not again start with sc.parallelize because that RDD is already persisted in memory. So I could just be doing a b.count where it will get the persisted RDD from memory and give me a count. So if we do this and we go back here in my jobs, it shows me the second job. Look at the time difference. So this is 2 seconds and this is 0.2 seconds. And if we look at this one, it basically says the input is 175 bytes. Now that's what we know, that RDD was cached in memory and we are benefiting from caching. So this is a simple example of using storage level where I could have written the whole code in basically a file and done it. Now as it says, you can also do a get storage level, so you know which RDD you have persisted. And basically you can, if you would want to check that. So we have b.get and then I can do a tab which shows me different options. So we will use storage level to basically see what was the storage level, and it basically based on different storage levels, it gives me when we used memory only, it shows the value as true. So you can also be looking at the storage level here. You can be printing out the storage level if you would be interested in doing that. So the same thing, what I have b.get storage level, I could just wrap it using a print to see what it shows here. And that shows me memory serialized with 1x replicated. That means it was not replicated. So I could be using storage and then I could be using memory and disk too. So that's one more option which you can do. And then you can see how is it cached, where is it cached, where is it persisted, right? So that's an example of your storage level. Now, when we talk about PySpark, it also has something called as data frames, and we'll look at that. So when you're working with Spark, Spark's basic or core API was RDD, and then there were higher level APIs, that is data frames and data sets, which were introduced as experimental features in Spark 1.6, but then they became the main APIs which are extensively used these days when you're working with structured data, and they were introduced from Spark 2 onwards. Now PySpark, or basically using Python, you can also be working with data frames, and data frames is basically a structured way of looking at data. Or you could say, if your data is already structured, it would be good to inform about the structure and format to the backend DAG scheduler, and then it would be more efficient in accessing the data. Now when you talk about data frames in PySpark, data frame is basically a distributed collection of rows with named columns. Now that's what you would have seen if you have worked with Python's pandas library, or you can be using or creating data frames using Scala as a programming language. So data frames is basically a table of data with rows and columns. Now when you talk about RDDs, we know that they are immutable in nature by default. If you are working on a collection of elements, you could basically have mutable or immutable structures created. But when you talk about RDDs, these are immutable in nature. You have basically lazy evaluation. So RDDs are lazily evaluated and they are distributed across memory. So when you talk about creating data frames in Spark, you can be creating using different data formats. You can be loading data from existing RDD. You can also be programmatically specifying schema. So there are different ways in which you can work with data frames. So let me quickly show you an example here. Now when we go to our machine and let's get to PySpark. So here I'll just say bin/PySpark. That brings my Python prompt to basically allow you to work with Spark. Now as I said, your Spark context gets initialized automatically, and when you use a method of Spark context, you are moreover working with RDDs. And if you would be interested in working with structured data, then you would be using Spark session. So for example, what we can do is we can say x equals, and then I can just say Spark dot, and then I can check what are the methods available here. So you do have a method which is called create data frame. Now we would be interested in reading a file which might be say JSON or a CSV file and then creating a data frame out of it. So we can do that using read, and then I can again say what are the methods which are available with read. So you have an option like format which can be used, or you can straight away be using CSV or JSON or text or ORC. So I can say format, and for now I will select a JSON file. And what I would also do is I would want to infer the schema. So I can basically use option, and with option I can say, for example, infer schema, and then I can say true. What I can also do is I can specify one more option, and I can say header. If there is a header, then I can set it to true. If there is no header, then basically it will just look at your data, and then we can do a load where we would want to point to a file. So I'll say home/hdu/sample files, and here I have a file people.json which does not have huge data. We can take a look at bigger data set also, and here when I do this would have created or should create a data frame. So data frame where it infers the schema, where it understands the first row as the header, and it creates a data frame. And whenever you would want to look at a data frame, I could just do a x.show that shows me it is a data frame which has got created. Now since we are in Python, we could do a type, and that shows me it was a data frame created. You can straight away start doing a select, and here I could say, for example, show me the age. Now at this point of time, if I do not do a show, then it just shows me that it is a data frame and it has one field, and that's of the type bigint. So I could again do a show, and that shows me the result of data frame. So you can be then doing multiple other operations. You can do a filter, you can basically do a group by, you can do a count. So you can do all that, and if you have any doubt, just do a tab and it will show you what are the options. For example, I'll say let me get age which is greater than 19, and here you are working on basically a string. So you can do these things, but then you will have to follow different syntax. But if you see x dot, and then I can search what are the different options which are available, so only the syntax has to be corrected. But then I have something called as x dot filter, and then basically I can be specifying what I would be interested in and then filter out the values. Okay, now this is basically a data frame. So similarly, I can be also looking at a bigger file. For example, let's say I have a file called bank_full1.csv, if I'm right. And then we can basically point this to format as being CSV. Let's quickly check if we have this file. So let me open up a new terminal. I look into the sample files, and I have a bank_full.csv. So that's the file I'm interested in, and that's a CSV file, unless like last time we saw a JSON file. And here we gave the path which is wrong, and that's why it was giving me an error. So let's go back here and change this to the right path, and then basically it should create a data frame out of this. If I do a x.show, that should show me the data frame, and by default when you look at your data frame, it shows me only the top 20 rows. And then you can start doing a select on this, you can filter the data, you can do a group by, you can do operations, you can do functions on it, and you can do various ways in working with a data frame. So this is just a simple example of using PySpark to create a data frame, and then you can start doing your other operations on it. Now, when it comes to your broadcast and accumulator, so broadcast variable allows the programmers to keep a read-only variable cached on each machine rather than shipping a copy of it with tasks. Now, why do we need this? So, for example, you are doing a bigger operation such as join or union on two RDDs or two data sets or two data frames. Now, in that case, we know that whenever we basically have a data frame created or an RDD created, it would have partitions. So for example, we had this here, and I can do a X dot and check what are the different ways in which I can be looking at this. So as I said, by default, each RDD or data frame which gets created, that would have your partitions. Now you could convert your X into say an RDD if you would want to do it, right? And then basically I could have done this by saying Y equals, right? And then you can check at your Y what are the different options, like you have get num partitions, right? So I could just do this one and I could see how many partitions are created. So that was a big file, and it shows me there is only one partition created, right? So based on the partition, you would have the number of tasks. Now, if you have multiple data frames or data sets on which you would want to do a join operation, then the point here is that if both are large, and if you would be doing a join based on a particular column, now in that case, there would be a lot of shuffling involved. So basically, if you have your data in the form of a pair RDD, or if you have your data frames where you would want to do join on a particular column, it would have to shuffle the data for both the data sets or data frames or RDDs so that it can be doing your operation. Now in that case, we can always use a broadcast variable, and in that what happens is that the smaller data set or data frame can be converted as a broadcast variable, and then this variable is shipped to the memory of each machine, which can then be used to directly do your join or other operations with the variable or with the smaller set of data in memory with the larger data set on that particular node. Now that's where broadcast variables are useful. So for example, you can be saying dot broadcast. So like what we were doing earlier, you can create a Spark context. You can say broadcast, and I would want to broadcast this particular list as a variable. Now you can always be looking at the value of it. Okay. Now once this broadcast variable is created, we can then be using this. So for example, B is my broadcast variable and A could be a huge list of elements. And if I would want to do a join or some other operation between them, then this B would be shipped to the memory of every node. Now what would have happened is on every worker node, the memory would have a partition of your larger data set. So this small variable or this broadcast variable having less number of values could be used to do a join operation with each partition on each node. Now that's the benefit of broadcast. Now when you talk about accumulators, these are variables that are only added through an associative and commutative operation. So for example, if I would want to use accumulator, so here I would say sc.accumulator. Now I'm defining a function here. So I'm specifying global num, and then I would want to increment the value of num based on x. Now here you create an RDD. So you say sc.parallelize on a particular number, and for each element here you would want to apply this particular function. So basically this function which takes x as a value and it keeps adding all the values, we are applying this function to every element in the list. So once we start iterating through the list, 20 would get added to 30, then the total would get added to 40, and so on. Or you could say other way, that you will start with 20 and then 30 plus 20 and then 40 is added to the sum, 50 is added to the sum, and finally look at the value. So when you're talking about accumulators here, so we can basically looking at the accumulator value here, which would show me 150. So you can try this out like what I've shown other examples, either this one or the broadcast, and basically you will get a better idea of how broadcast variables and how your accumulators work. So moving forward, now that we have looked at broadcast and accumulators, let's also look at some sub packages in PySpark. Now, as I said, whether you work with Python or Scala or R or Spark SQL, you have Spark has different components which allows you to handle different kind of workloads, handle different kind of work packages, and work on different kind of data sets. So when you work with PySpark, it has a component for SQL. So you can also be using PySpark.sql module, and that basically allows you to work with structured data like what we were seeing an example of data frames. You could be using PySpark.streaming module, and that is if you are interested in working on streaming kind of data, wherein you could be doing stream processing. If you would be interested in building machine learning algorithms, then you can use PySpark's.ml package and also the MLlib package. So these are two different packages, one mainly for data frames and one with other machine learning algorithms. So there are a lot of sub packages in PySpark which you can use, and you can be appropriately using the modules. Now there are different companies which are using PySpark, and I would say all the companies which are using Spark would be having their applications either in Scala or written in Python, where they would be benefiting from PySpark or Spark Shell and thus working on structured data. So you have MLlib. Now that's basically where Spark started. You have Mindtree, you have Walmart, Repro, Tech Systems, Tridence, Capgemini, Alibaba, and many more. So there are different other companies which are using PySpark. Now to look at the demo, we can be looking at a particular data set, and then we can see how we can use PySpark to analyze that particular data. Now for our demo, we will look at this Walmart stock related data what we have, and this is basically saved in a CSV format. So as I showed earlier, we can be using the CSV format, we can create a data frame out of it, and then we can basically ask some questions to it. So for example, if I would be interested in working on this one, so here if you see, I have imported find Spark and I have initialized it, and then from PySpark I'm using the SQL module where I import Spark session, and then I can be doing a Spark session builder, app name, Walmart. I can just say get or create. Now you would not be doing all these things if you were working in an interactive way like I was showing in our Spark setup. So you could straight away start from here where you are reading a file into a data frame. So you could be loading the data. Now if that data is existing, so here in this step you are basically doing a read.csv. You are pointing it to a file wherever your data is stored, and then you say infer schema and you say header true so that it knows the first row is basically your heading. Now once you're done with this, now in certain cases if you're using a notebook to do it, or if you would want to do it from your command line, right? Now in that case you will have to make sure that if you're doing it from the command line, you will have to get these packages. So for example, what I can do is I can be going into, say in my case I have Anaconda installed, and that's where I'm showing you this notebook. So what you can be doing is go into your Anaconda prompt if Anaconda is installed, or if you have your Python, then you can just be doing a pip install find Spark. You can be doing a pip install PySpark, and it should get your modules. And then it also installs Py4j, which I was explaining earlier. It will basically set up all these packages. So Py4j and PySpark shows you the version, and then you should be all set. So if you're using Anaconda, which has basically all these different ways of working with your Python, so you have Jupyter, you have basically Spider, you have Visual Studio Code. So if you would want to use Anaconda, then just install Anaconda Navigator where you can use Notebook. Then you can also get to your Anaconda prompt and install the packages, and then you can start your Jupyter Notebook. So here you could be doing this. Other way is you could be doing it from your command line, provided you have installed these packages. The third way is you can be doing it from your Spark standalone cluster, and in that case you don't have to do all this stuff. You can straight straight away start reading the CSV and then start working on it. So here we are reading a Walmart file. Now this is what we have open. What was the open price? What was the high, low, and closing price, right? Shows me the date and it shows me the volume. So if you want to do some analysis on it, so you can create a data frame out of it. Then you can be looking at the columns, what are part of those data frames. You could be just looking at the first row of the data frame using head, and you can see the values. You can check the schema using a print schema. You can be printing in first 5 rows. So for line in the data frame dot head, and you are saying I would want to look at first 5 rows and I would want to print it in line by line. Now I can be getting some general statistics out, so I can just be using a data frames.describe. Now that's the method which gives you just a summary, right? So when you are looking at these values, so it gives you count and mean, standard deviation, minimum, max. So that's like your finum summary or your describe summary. You could also be formatting columns to just show 2 decimal places. So here I'm using from PySpark.sql functions within the SQL package. I'm importing format number, and what I'm doing is I'm doing a describe to look at the stats, and then for the same stats I would be doing a select where I would be interested in looking at this summary, and what I would want is all of these columns which we were seeing here, open, high, low, close, volume, all of these I would want to just look at values with 2 decimal points. So I'm just specifying from my data frame what is the column name, how do you want to cast it as, and basically giving the limit, and then I'm saying what would be this called. So you could change the name if you would wish to, and here we have reduced the information what we were seeing here just to 2 decimal points. So this is a simple example where you're doing some formatting. Now you can create a new data frame with a column called HB ratio. That is ratio of high price versus volume of stock. And how do you do that? You use the with column method. So with column method. Now here we are doing this. Now with column, I could also be passing a function if I have created my user defined function. So here I am saying df, that's my data frame. I say with column. What would be my column called? So that's your HV ratio. Now how do you get that? So out of your data frame, you take the high column, divide that with the volume, right? And then you would basically do a select on this HV ratio. So what we are doing is we are not only in this part creating a new column into the data frame. So this data frame df underscore HV, the new one, will have this particular column. And what we are doing is with this with column, it would have added HV ratio as a column in your data frame. And then I'm just doing a select on that. So here it shows me the HV ratio and the values. So if you would want to answer some more questions like which day has the peak high in price, you can do an order by. So here you're again working on your data frame. You say df, you would be interested in looking at the high column. You would want to sort it in a descending way, and then whatever is the result, you would want to basically select the date and head value for your first index position. So you could also be doing a mean of the close column. So here we are using import mean, and then we are applying the mean function on the close value. What is the maximum and minimum value of volume column? So you could be doing this by just doing import minimum and max and apply this on your volume column. How many days did the stock close lower than $60? And you can be looking at 60, and you can be doing a filter. So what percentage of time was high greater than $80? Again, you're doing some computation on the high column where you're looking for the value which is greater than 80, which is given in this brackets, and you're doing a filter. What is the Pearson correlation between high and volume? So you can just use the correlation method here on high and volume column, and you can get the value. You can import correlation, and you could also be doing it in this way where you could do a df.select, use the correlation method, or you can say function on high and volume, and then basically show the results. If you would want to find out what is the max high per year, now in this case you would be importing some other packages like day of month, hour, day of year. You have month, year, week of year, and so on, and then you are using with column where you are creating year and you are extracting the year aspect from the date, and that would become your year column. And then what you're doing is using this year column, you're doing a group by and finding out the max high value per year. So what is the average close for each calendar month? And basically you create a month column using with column by extracting the month out of this date, and then you do a group by month and do a mean, or order by month, and then you can do an average close. So these are different ways in which you can answer questions on a particular data set using PySpark. And then obviously once you have run this, you can always go to the Spark UI and basically look at this. So this code will be available for you, and here you can always look at this, which basically gives me an idea of working with your data frame using PySpark and different modules and functions and different packages which we are using to extract useful information from a particular data set. So this is your PySpark.
Let's have a quick look at some Spark interview questions, which will just prepare you with different aspects of Spark and its components and can help you when you're facing an interview. Now here we have some generic Spark questions such as, how is Apache Spark different from MapReduce? Now this is one of the common questions which you might be asked about. You would have to answer about differences between Apache Spark and MapReduce, right? Now MapReduce is a programming model and Apache Spark is a processing framework. So when we talk about Spark, you can basically say that Spark processes data in batch, but then it is also good for real-time processing. In fact, it is one of the features of Spark that it is good with real-time or faster processing. Spark runs nearly 100 times faster than Hadoop MapReduce. Well, that actually depends on how your Spark application has been written and in comparison to how your MapReduce application has been written. But then if you would say Spark application, whether that is written in Scala, Python, your R, in any way, if it has been well written, then Spark can give you a performance benefit. It would be 100 times faster than your traditional MapReduce. Now Spark, as I mentioned earlier, does not have its own storage. So for processing, it would be picking up the data from, say, an RDBMS or from Hadoop distributed file system or from a data warehouse package such as Hive. But then Spark is known to do a in-memory processing. Now it stores data in RAM in the form of RDDs, and that is why it gives you a faster performance. Now when you talk about MapReduce is slower due to the reason that it has two phases, mapping and reducing, wherein the intermittent result, that is the result of your map phase, is basically written to HDFS and then it is picked up from HDFS for your further reducing. So MapReduce also processes the data stored in HDFS, but as I mentioned, while processing also, the staging data or the data which is result of map phase and has to be picked up by reduce phase is also stored in HDFS. Spark also has features such as caching and in-memory data storage. So you can have your computations, that is the result of RDDs, getting stored in cache. Now that could be different ways. So you can use a storage level and then you can specify whether the caching is going to be in memory, is it going to be in disk, or is it going to be a combination of memory and disk, but those possibilities are there in Spark. Now MapReduce does not have this. Well, you have a feature of distributed cache, but that's not as efficient as Spark. So Hadoop is highly disk dependent. Now, if somebody asks you what are the important components of Spark ecosystem, so Spark basically has language support for different programming languages such as Java, Python, Scala, and even R programming language. And Spark has different components for different use cases and different kind of data. So it has a core API, that is your Spark core engine. You have Spark SQL to process your structured data. You have Spark Streaming, which helps you in processing streaming data. MLlib to create your machine learning algorithms by using different statistical methods and algorithms which are available. And GraphX, which is for your graph-based processing. Now, when you talk about Spark, it can be set up as a standalone cluster, that is having one master and multiple worker nodes. It can be integrated with Apache Mesos, and then you also have Yarn with which your Spark cluster can be integrated. So if you are describing about important components of Spark ecosystem, then you will mainly speak about the mid layer, that is the core components. You could also speak about your language support and the cluster management solutions which can be used when you're working with Spark. Explain how Spark runs applications with the help of its architecture. Now, when we talk about Spark application, it runs basically as independent processes, or basically you have application which would be split into tasks, and these tasks would be running across your different machines. Now, you could have basically Spark session or your Spark context, which are these important classes, or you can say the entry point of your Spark applications. Every Spark application would have a driver, and what does that driver have? It basically knows the flow of your application. At the back end, you also have a DAG scheduler. So for all the steps what you're doing in your application, DAG scheduler is aware of what are the different steps which make your DAG, that is direct acyclic graph, for your in-memory processing. Now your Spark session or your Spark context, which is your entry point of your application, interacts with the cluster manager. Now in this case, we can be specifically speaking about Yarn, which has resource manager as the master of the cluster and node manager as the slaves of the cluster. So your Spark session or Spark context speaks to resource manager, that is the cluster manager, which basically would request resources from the worker nodes where the execution would happen. Now, worker nodes would have a processing slave, that is node manager, which grants the approval of usage of resources to resource manager. Now, this request which we are talking about, that is requesting resources, is called container. So resource manager requests containers from one or multiple worker nodes. Worker nodes or the node manager process running on them grants these containers, and it is within these containers a executor process is launched, which is responsible to take care of the application related tasks. So when you talk about iterative algorithms, they apply operations repeatedly to the data, and they can benefit from caching data sets across iterations. So you can also have the RDDs which are created or the computations which are done. They could be cached, and this cache can be beneficial for your further run of the similar tasks or similar computation. Now, what is a task here? It is basically the unit of work to the data which is coming from the respective disk to basically transform or work on it. So when you talk about execution, which is taken care by executors, which could be either one or multiple on a particular node, now which depends basically on the data on the node, which depends on the resources available on the node. You could have multiple executors. The result is then sent back to the driver, and that's how your application execution happens in case of Spark. One of the common questions which is asked is, what are the different cluster managers available in Apache Spark, or how does Spark work with different setups? So by default, you can have Spark in a standalone mode. This basically means Spark would be running with one master and multiple worker nodes, with one master and multiple worker processes across machines. You would not have any Hadoop setup or Mesos or anything else. So by default here, applications would be submitted to the standalone mode, and they would run in a FIFO order, that is first in, first out, and each application would try to use the resources on available worker nodes. Spark can also be integrated with Apache Mesos, and that's an open source project to manage computer clusters and can also run Hadoop applications. In fact, Spark initially came into existence to prove the credibility of Apache Spark, and then later became a independent project. You have Spark integration with Hadoop Yarn, so that is where Yarn is taking care of resource allocation in a Hadoop cluster, and Spark leverages the benefit of using Yarn. You could also have Spark working in a Kubernetes environment. Now, Kubernetes is an open source system for automating deployment, running your microservices, scaling and management of containerized applications. So Spark can even work in a Kubernetes setup. One of the important things of Spark, which really makes it powerful, is lazy evaluation. So what is lazy evaluation in Spark? When Spark operates on any data set, that is the data which you are interested in processing, it would take care of the processing based on various steps within your application. Each step basically creates a RDD, a resilient distributed data set. So for example, if I would want to read a file, I could use a method of Spark context called text file, and this would create an RDD. Then you could do a map or a flat map or a filter, and all these steps, what you code in your application, are lazily evaluated. That is, they are not evaluated as soon as the step is created. They are evaluated, they are executed only when action is invoked. So whenever you do a transformation such as map or filter or flat map, or you just use a method of Spark context, in this case it will only and only create an RDD, a resilient distributed data set which exists in the memory. But this RDD does not have any data loaded, does not have any transformation done. So transformations in Spark are evaluated only when one would invoke an action. So till then it is called as lazy evaluation, that is, it does not evaluate the file which you are processing or any map or filter or any other transformation. So the question is, what makes Spark good at low latency workloads like graph processing and machine learning? So how does Spark achieve that? So as we discussed earlier, your Apache Spark is good in storing data in memory for faster processing and model building. So any component of Spark you use, such as Spark SQL, Spark Core, Spark MLlib, Spark Streaming, or GraphX, in any of these cases it is in-memory processing. That means the data is loaded into the memory of the respective worker nodes, and then the processing happens. Plus the data which is loaded in memory, which is undergoing some transformations and results in some kind of intermittent data, that data can be stored or cached in memory for further processing. When you talk about machine learning algorithms require sometimes multiple iterations to create a optimal model. Even your graph algorithms traverse all the nodes and edges. So basically, these low latency work nodes that need multiple iterations can lead to an increased performance because you are doing the processing in smaller iterations by loading data in the memory. So there is also a concept of automatic cleanups. So the question is, how can you trigger automatic cleanups in Spark to handle accumulated metadata? And there is a parameter, or you can say property, which needs to be set. To trigger the cleanups, you need to set parameter spark.cleaner.ttlx, time to live, and that's where your job which is running, which is divided into batches and writes the data to the disk, you could trigger a cleanup based on this parameter. Now, how do you connect Spark to Apache Mesos? So suppose you have Apache Mesos set up, but then you would also want to do in-memory processing using Spark. How do you do it? So first thing what we will have to do here is configure the Spark driver program to basically connect to Apache Mesos. That is, you have to give your connection details to connect to Apache Mesos. Then you will have to put your Spark binary package, that is Spark installation package or binary package, in a location accessible by Mesos. So Mesos knows that where Spark is existing. Spark can install in the same location as that of Apache Mesos. And then you can also configure some properties which says what is the Spark Mesos executor home, pointing to location where Spark is installed. So basically your Apache Mesos has to be informed about Spark, and Spark can be existing with Apache Mesos or within Apache Mesos so that it can use Apache Mesos. Now, one more question which you can expect in interview or if somebody is testing your knowledge is about different data formats. Now, other than your regular formats such as JSON, XML, text, CSV, there are other intelligent formats such as binary files or sequence file formats. You have Avro, you have Parquet, and so on. So Parquet is basically columnar format which is supported by several data processing systems. So if you have, say for example, you have data which is in CSV which has multiple fields or multiple columns, and you do not access all the fields or all the columns all the time, it would be advisable to go for a Parquet format wherein Spark can perform read and write operations by default. That is, whenever Spark tries to read a data set, it will assume that data is in a Parquet format. And if your data is in a different format, then you have to specify that. So advantages of having a columnar storage is you can fetch specific columns for access. It consumes less space, obviously, brings down your disk usage by 62% approximately. It follows type specific encoding and controls your IO operations. So if you would be interested in reading about different formats, I can share a good link with you which talks about formats, and here you can find, let's look at formats. This is the good link which basically shows you details about different data formats such as compression schemes. You have metadata management, you have different common file formats, you have binary files or sequence file formats which can be compressed at a block level or record level and support splittability. You also have other formats such as Avro and Parquet, and this is a very good document you can refer to. Now, coming back, let's look at the next question. So what is shuffling in Spark and when does this happen? Now, shuffling, as we know, would basically mean similar kind of data being brought together. So shuffling is the process of redistributing your data across partitions. Now, what we know is whenever we do a transformation, whenever we use a method of Spark, what does it do? It creates an RDD. Now, unless and until you have specified how many logical partitions of that RDD you want, it will by default create number of partitions based on either the data set size or based on the number of cores which are available in your cluster, or it could be that you are basically creating partitions by default, that is 2. So say for example you have a data which you would want to process, and that data is converted into a key value pair. So take an example, you have a sentence, welcome to my world. Now if I want to split this in a key value combination where I would say my first word will become the key and the complete line becomes the value. So my key would be welcome and the value would be welcome to my world. Now, if you have similar data like this, which is key value pairs, and that is because of some transformation you did on a data set, all this data would be in a RDD during the time of evaluation. And this RDD would have partitions. So you would have some key value pairs in partition 1, some key value pairs in partition 2. Now, suppose you would want to do something like a join, or suppose you want to do a group by or a sort by based on key. Now, how would that happen? That would be possible when the similar keys are brought into the same partition. So that will trigger shuffling so that your key value pairs, which are stored in RDD, in partitions, you will have your similar keys shuffled and brought to the same partition, where then you can do some key based operations. Now that's where your shuffling in Spark happens. There is also an operation called coalesce, and why is that used in Spark? So Spark uses coalesce method to reduce the number of partitions in a data frame. Now what we know is whenever you're working on structured data, and this structured data, basically whenever you do a transformation on it, it creates a schema RDD, or what we call as data frame. So what is data frame? Like a table which has rows and columns with headings. So coalesce is basically used to reduce the number of partitions in a data frame. So for example, you have 4 partitions which have some values, and what you would want to do is you would want to filter the data in such a way that you will remove the multiples of 10. So here you see we can be using coalesce for this, which will remove all the values which are multiples of 10. So data is read from a CSV into an RDD. The RDD has some empty partitions. It makes sense to reduce the number of partitions. Why not? And using coalesce, you can bring your data together in less number of partitions and get rid of the partitions which really do not have any data. Now the question is, how can you calculate the executor memory, or calculate the memory which will be required by the executors which will take care of your tasks?
Okay, so let's continue learning on some Spark interview questions. Now here's our next question. So how can you calculate the executor memory, right? Now when you talk about executor, it is the JVM process which will take care of your Spark application related tasks that would be executed. So let's say this is your cluster. So you have 10 nodes, each node has 16 cores. That is, you can then take away 1 for your operating system itself. Each node has RAM, which is 61 gigabyte of RAM. And when you talk about your cores is the number of concurrent tasks an executor can run in parallel. So the general rule of thumb for optimal value is 5. Now it depends. Now when you talk about number of executor identification, how do you do that? So number of executors is equal to number of cores that the machine has divided by the concurrent tasks. So if we say we have 15 cores and we have 5 concurrent tasks, so we get number of executors is 3. And depending on the number of nodes you have, you can multiply that with the number of executor in each node which would run for your data processing, and that will give you number of executors for your Spark job. So in our case, we have 10 nodes. We are talking about the number of executor in each node, which we just calculated as 3, and then that gives me the total number of executors, right? Now this is how you can basically calculate the executor related memory. Now let's look at some Spark core questions. So what are the various functionalities supported by Spark core? So what is Spark core? Spark core is the engine for parallel and distributed processing of large data sets. So you could be scheduling and monitoring your jobs, you could be doing memory management, fault recovery, and task dispatching. So these are various functionalities which are supported by your Spark core. Now, what is the significance of RDDs? That is your resilient distributed data sets in Spark. Now, RDDs are the building blocks in Spark. So Spark core is embedded with RDDs, which is basically the fundamental data structure of Apache Spark. What are RDDs? These are immutable, fault-tolerant, distributed collection of objects that can be operated in parallel. And when are these RDDs getting created? Whenever you do some transformation. So either you would be using a method of Spark context, or say the initial entry point for your application, that's your Spark context. So methods could be something like text file, whole text file, parallelize, and so on. Or you could be doing some series of transformations. So per transformation you do on your RDD, it creates a further RDD. So you could be doing a map, flat map, filter, and many more. So RDDs by default, whenever they are created, they are split into what we call as logical partitions. Now, when we are creating an RDD, we could also mention how many partitions we want. So RDDs are split into partitions and they can be executed on different nodes of a cluster. How do you convert a Spark RDD into a data frame? Now, we know that Spark core comes with the RDD concept, that Spark RDD is the basic API, and then you have other APIs in Spark such as data frame and data sets. So if you would want to convert a RDD into data frame, you could be using a helper function called 2df. So here we are importing a package and then we would want to create a data frame. So we use the Spark context. We load from MapRDB. So we basically are getting the data from a table. We are also giving some conditions like where field is something. You're doing a select, and finally you're doing a 2 data frame which will convert your RDD into a data frame. Now you could also be doing that using Spark sessions method create data frame. So as we know that when you work with Spark RDD, you use Spark context, and when you would want to work with Spark SQL, you would be using the internal class that is Spark session, and that has different methods. So you could be creating a data frame using create data frame. So you can convert an RDD of row to a data frame by calling create data frame on a Spark session object. Looking further, so if somebody asks you, explain 2 types of operations supported by RDDs. Now, as I said earlier, RDDs are created either when you use a Spark context and a method of Spark context like text file, parallelize, whole text files, or when you do some transformations. So there are 2 kinds of operations which are mainly supported by RDDs. One is your transformations and second is your action. So any or every transformation you do, it will only result in an RDD, which basically means a logical step, but there will be no execution happening. So your transformations are operations that are performed on an RDD to create a new RDD. How is this RDD initially coming into existence? So if I would have said val x equals sc.text file and then I pass a file into that, that would create an RDD. Or if I do a sc.parallelize, or if I do sc.whole text files or a sequence file, so that would have created my initial RDD, and then I could be doing any transformations on that. You could also be doing the second kind of operation which actually leads to the execution of your Spark DAG, and that's your actions. So whenever you launch an action, you would have your Spark application application's execution happening. So when you talk about actions, it could be take, it could be collect, it could be reduce, it could be first, count, and so on. So these are your two kinds of operations which are supported by RDDs. Now, how do you programmatically specify schema for a data frame? So we know that we can be reading, say, CSV or text or JSON or Avro or Parquet. So you could be reading any kind of data in different data format, and if you use Spark sessions method like read or read.format.load, now that creates a data frame. But sometimes you may be interested in working on a data where you would want to specify the schema for every field that data has. For example, you have a list which has ID, name, and salary, and what you want to do is you want to assign a schema to it, and that can again be done in two ways. One, you can be creating a case class and then passing in the schema to every field, or you could be using struct field. So here we are doing a dot map. We are selecting every field, and then we are using a struct field which will basically get the data type and apply that to every field. What is a lineage graph? Now, when you talk about Spark, as I said, every step you do in a Spark application, starting from your initialization or starting from using your Spark context method, it creates a RDD, and each RDD is like a logical step in your Spark application's DAG, right? So when you talk about Spark application's DAG, it has series of steps which you have coded, which have either a method of Spark context or series of transformation. So this whole DAG is basically like a lineage graph. Now, Spark does not support data replication in the memory. Well, we can have persistence, which can be done. So if you would want Spark to benefit from a RDD graph or a RDD lineage which was already created, then Spark has an internal way of capturing the lineage of your steps. So lineage is basically a flow. So it is also called an RDD operator graph or RDD dependency graph. Now let's look at some Spark streaming questions. So one of the question is, what do you understand by D streams in Spark? So when you are working on streaming data, or when you intend to process streaming data, you would be interested in capturing the data at various time intervals. Now, your D streams or discretized streams is basically the abstraction. So what happens is, when you have a continuous stream of data that is coming in as input, coming from some source, or you have a process data stream by some application, this data stream or this input stream is broken down into smaller batches of data, and these smaller batches are called your D streams. So if we see here, we see data from time 0 to 1, 1 to 2, 2 to 3, and 3 to 4. So this is nothing but my D streams, and each D stream is a smaller batch of data on which you would have series of transformations which will be applied based on what you have coded in your Spark applications. Now, let's learn about caching in Spark streaming. So if somebody says, what is caching in Spark streaming? So we know Spark does in-memory processing. So does it have caching? Yes. So that is your persistence. So caching is also known as persistence or optimization technique for Spark computations. So basically, when you have your processing happening from one D stream to other D stream, you could have persistence implemented. Now that helps you to save interim partial results so that they can be, if required, reused in subsequent stages. So when we talk about the default persistence level, that is to set to replicate the data to 2 nodes for fault tolerance. So when you have your streaming and stream processing happening, we can have the persistence of that computation across nodes. Now, one of the main problems which also is seen when you talk about Spark application is operations like joins. So if you intend to do joins across multiple RDDs, one of the problem it poses is that, first of all, the RDDs which you are working on should be like a pair RDD, or what we call as a key value pair RDD. And if you do something like join, then in that case, in every RDD, which is nothing but a pair RDD, or you can say the data within the RDD is in the form of key value pairs. So all the similar keys, and we know that RDDs have partitions. So all the similar keys have to be shuffled across partitions so that similar keys land in the same partition. Now this would be happening on other RDD also, which you would want to join. So you have RDD1, which has partitions, and this RDD1 has key value pair, and all the keys have to be sorted and brought into same partition. Similarly, it will be on the second RDD, and then a join can happen. So this can be triggering a lot of shuffling, which would be happening when you're doing a join kind of operation. Now that could be tackled by using broadcast variables. So basically this one allows the programmer to keep a read-only variable cached on each machine rather than shipping a copy of it. So you could be creating a broadcast variable, and this broadcast variable can be used in operations like join. So this broadcast variable will then be shipped to memory of every node. So if you do a join in two RDDs, one of the RDDs can be broadcasted as a broadcast variable, and when you do a join using this broadcast variable and the other RDD, it will be faster, it will avoid a lot of shuffling, and then you could do your operations more efficiently. So which transformation returns a new D stream by selecting only those records of source D stream for which function returns true? So if we have this question, so the answer would be filter. So filter transformation will give a new D stream by selecting only those records of source D stream for which function returns true. Now, does Apache Spark provide checkpoints? And the answer is yes, there is a checkpointing mechanism which can be used in streaming. So Apache Spark provides an API for adding and managing checkpoints. So checkpointing is the process of making your streaming applications resilient to failures. So you could be creating a streaming context. You could set also a checkpoint path, and you could define a D stream. So when you start your streaming application, it will not only be capturing data at regular intervals based on how your receiver has been set, but you could also have a checkpointing mechanism which makes sure that every computation which happens over a D stream can then be using a checkpoint mechanism if any kind of recovery is required. What do you mean by sliding window operation? Now that's one more extensibility of your Spark streaming. So you can not only do streaming at regular intervals using your Spark streaming context, but then you can also control the transmission of data packets between multiple networks. You could be using Spark streaming for it. So Spark streaming library provides windowed computations. So windowed computations basically means a set of intervals for which the data was received, and you would want to do a processing based, a window based operation. It will look at the last three instances, and then it gives you a window based output. So that's your windowing. Now, what are the different levels of persistence in Spark? So Spark, as we know, whatever steps you create in your application, those steps lead to an RDD whenever you're doing some transformation and using a method of Spark context. But if you are triggering an action, that basically triggers the execution of your application. Now, at certain times, in some steps, whatever computation was done, you may want to use the same computation again down your application. Now, in that case, caching can benefit. So you could do persistence. By default, it is memory, but then you could use all these different options of storage level, such as disk only. So you can have the RDDs or the computations stored on the disk. You could have memory only in a serialized way. So that is storing the RDD as serialized Java objects with 1 byte array per partition. You have memory only, that is storing the RDDs as deserialized Java objects in the JVM. And if an RDD is or cannot fit into memory, it will be recomputed. Now you could have something like off heap. So it works with memory only serialization, but stores the data in off heap memory. You have memory and disk, and you can choose the percentage. So memory and disk basically means the RDDs which are getting created as a part of your application, those RDDs are stored as deserialized Java objects. And if in case the RDD is not able to fit in the memory, additional partitions are stored on the disk. So you could also have memory and disk serialized. So all of these come with storage level, and this is how you can have persistence achieved in Spark, where you would want to persist some RDD computations. Now, somebody might ask you a difference between different transformations, like you have map and flat map. So what's the difference? Whether it is Spark streaming or Spark core. So when you talk about your map function, it basically, in terms of Spark streaming, gives you a new D stream by passing each element of the source D stream through a function. So technically speaking, you are applying a function on that D stream which is getting collected or which is getting created. Now Spark map function, what does it do? It takes one element at a time, and based on whatever you have given in your code, it applies that function of the data it takes every time, or of the element it takes every time. When you talk about flat map, it is basically a combination of map and flattening, or it is basically flat map does the flattening. So it is similar to map function. It applies the function to each element of RDD. So your flat map allows returning 0, 1 or more elements from the map function. So it is basically flattening it, or it is splitting your data into individual elements. Now, how do you compute the total count of unique words in Spark? So this is basically you doing a word count in Spark. Now in layman terms, you could take a file. Depending on if you're doing a word count, you would want to split that file and get individual words in the file. And then you would want to write some kind of loop which looks into these words and does a counting of these words if the words are repetitive. So you can load the file as RDD using sc.text file. You could then apply a function to the particular line. So you could be doing a tokenizing, that is splitting your line into individual words. Then you could do a flat map so that you can get all the words split and exploded or extracted from the file. You could convert each word into a key value pair, because you remember we are doing a word count. So we can have a key value pair where key is the word and the value is, say, number 1, which is assigned to every word. Then you could be doing a reduce by key action. So reduce by key action is basically going to reduce the data based on the keys and give you a total. Okay. And finally you can print the result. So this is how you can do a word count in Spark. So suppose you have a huge text file. How will you check if particular keyword exists using Spark? And that's pretty simple. So you could already be doing a if line dot find and then give your keyword, and you could be pushing it to say -1. You could be doing a return 1 or return 0 depending on what you're trying to do. So here we are creating a function which basically takes the lines, does a map and applies a function called isFound, and then what it does is you want to search for a particular keyword. Now that could also be done using something like starts with or contains. So there are other ways in which also you can search for particular keyword that exists using Spark. Now, one of the important questions is, what is the role of accumulators in Spark? Now, like we discussed, broadcast variables, which are basically shipped into the memory of nodes and when can be useful when you would be using joins. Similarly, when you talk about accumulators, these are variables which are used for aggregating information across the executors. Now, this information can be about the data or API diagnosis, like how many records are corrupted or how many times a library API was called. And you can always look for this information in the Spark UI. So accumulators play an important role when it comes to aggregating information, which can then be used across executors. Let's look at some Spark MLlib questions. So basically, understanding about Spark MLlib or Spark ML library, which is used for machine learning algorithms. So what are the different MLlib tools available in Spark? Now, when you talk about ML algorithms, you have algorithms for different kind of statistical or machine learning problems, like you have classification, regression, clustering, and collaborative filtering. You also have for featureization, that is for feature extraction, transformation, dimensionality reduction, and selection of data. You have pipelines. These are tools for constructing, evaluating, and tuning ML pipelines. That is basically having a set of different algorithms which can be used. You have persistence, that is saving and loading algorithms, models, and pipelines. So you could always be persisting your algorithms. And you have utilities for linear algebra, statistics, and handling. So these are different tools which are available in MLlib in Spark. What are the different data types supported by Spark MLlib? Now this is again a common question asked. So Spark MLlib supports local vectors and matrices stored on a single machine, as well as distributed matrices. So you have local vector, which when you talk about local vector, that's a data type which MLlib supports. So MLlib supports two types of local vectors, which is dense and sparse. So if you would have vector in this particular form, you could create a dense format out of it or a sparse format. And if you talk about label point, which is mainly for your labels or responses, So this is a local vector which is either dense or sparse and mainly associated with label or response. So in binary classification, a label could be just 0 or 1. If you look at other data types, so you also have local matrix and distributed matrix. So Spark MLlib supports local vectors and matrices stored on a single machine as well as distributed matrices. So when you say local matrix, it has integer type row and column indices and double type values that is stored in a single machine. So here we are looking at a matrix of 3x2 size. And if you look in one dimensional array, this is how it would look. If you talk about distributed matrix, a distributed matrix has long type row and column indices and double type values. So it is stored in a distributed manner in one or more RDD. And there are various types of distributed matrix. So you have row matrix, you have indexed row matrix and coordinate matrix. For data types, you can always go and type say Spark MLlib data types, and that takes you to the Spark documentation wherein you can look at these different data types which we were talking about, like local vector, label point, local matrix and distributed matrix, and that basically has your 4 different types such as row, indexed, coordinate and block matrix. So moving further, what is a sparse vector? Now we were talking about local vector, local matrix which has dense and sparse vector. So sparse vector is a type of local vector which is represented by an indexed array and a value array. So for example, if we have sparse 1 and you create a sparse vector, so here 4 is the size of the vector, 1, 3 are ordered indices of the vector, and 3 and 4 are the value. So you have an indexed array and a value array which is represented by sparse vector. Now, if somebody asks you, describe how model creation works with MLlib and how the model is applied. So basically, Spark MLlib has 2 main components. It has a transformer. Now that's which reads a data frame and returns a new data frame with a specific transformation applied. Now that transformation could be anything. It could be map, it could be flat map, it could be filter, or you could have other transformations. When you talk about estimator is a machine learning algorithm that takes a data frame to train a model and returns the model as a transformer. So the output of estimator would be a model which could then be tested against our data. If you look at the model creation, and if somebody says how model creation works with MLlib and how model is applied, so Spark MLlib lets you combine multiple transformations into a pipeline to apply complex data transformations. Now, if you look at the image on the left, it says pipeline for training a model. So you would be looking at estimator. So you have a tokenizer, which will basically do the tokenizing or splitting of data. You have hashing TF, and then you are applying a logistic regression model. So this would be your estimator. Now you could have a transformer. So model produced can then be applied to live data. So that is, you have a pipeline model. So you are using, this would be called as a transformer. So you again have tokenizing, hashing TF, and you're applying a logistic regression model. Now, based on this pipeline where you have estimator, so you could be doing a fit method. So pipeline.fit, which will then be working on a raw text. It gives you, say, tokenized output, that is words. It will give you feature vectors, that is where you're doing featureization, and then you're solving the problem using logistic regression model. If you talk about pipeline model, so where we are talking about transformer, so you can say pipeline model.transform, and this basically will work on raw text, gives you words or feature vectors, and finally gives you the prediction. So this is how a model creation and application is done in MLlib. Now let's look at some Spark SQL questions. So Spark SQL is again an important component in Spark when it comes to processing your structured data. So what are the functions of Spark SQL? Now Spark SQL is a Apache Spark module for working with structured data or data which can be easily structurized. So what are the different functions here? You can load data from a variety of structured data sources. You can then query the data using SQL statement. So you could be having your SQL statements within a Spark program or from external tools that connect to Spark SQL through standard database connectors such as JDBC, ODBC. So you could be using Spark SQL to connect to, say, Hive data warehouse on top of Hadoop. It can be used to connect to RDBMS, and you can get in your structured data, or you could be accessing the structured data which lies on HDFS and then run your SQL queries, which would still be using Spark's in-memory processing capability. Your Spark SQL also provides rich integration between SQL and your other programming language code such as Python, Java, Scala, and so on. And you can also join RDDs and SQL tables and expose custom functions in SQL. So these are some of the functions, or you can say features, of Apache Spark SQL component. How do you connect Hive to Spark SQL? So we all know that when you work with Hive, Hive would have a Hive-site file, which would have different properties for Spark or for Hive. And this Hive-site file would also have the metadata information, or the location where Hive stores the metadata. And this particular config file of Hive needs to be placed in the config directory of Spark. Now, once you place this Hive-site file in the config directory of Spark, if you would use Spark, either Spark Shell or PySpark, or even running a Spark application, you could directly say spark.sql and then give your select queries targeting your Hive table. So this is how you can be directly working with Hive using Spark SQL. Now, one important question is, what is the role of Catalyst Optimizer in Spark SQL? So what does it do? Catalyst Optimizer, it basically leverages advanced programming language features such as Scala's pattern matching and CASI codes in a novel way to build an extensible query optimizer which is used by Spark SQL. So you would have your SQL query which is intending to access some data, and that would have some kind of unresolved logical plan to get to the data. Now, you also have metadata, which is stored in case of Hive, which Spark would need to access. So this unresolved logical plan is converted into a logical plan. Based on some logical optimization, you have optimized logical plan. Now, this plan is nothing but your execution path. So these physical plans, what we are talking about, use a cost model, and they select a physical plan which will be used to access the data, which is then used by RDDs, and the code is generated. So this is how Catalyst Optimizer performs or helps you in an optimized way of SQL query. Now, these are some examples here, and this shows how can you manipulate structured data using domain-specific language in Spark SQL. So Spark SQL, as I mentioned, allows you to work on structured data. Now you could be creating a data frame, which is a schema RDD. So you could be using Spark sessions method, which would be reading a file, or you might be interacting with directly Hive. In any of the cases, you would have a data frame. And then on the data frame, you could do a select and select a field. You could be selecting multiple fields and also do some computation. You could be doing a filter or a group by, and all of these functions work very well with your data frames. Finally, let's look at some Spark graphics questions to see how graphics helps us in graph-based processing. So what are the different type of operators provided by Apache graphics library? Now we know that Spark graphics will allow us to work on graph-based processing. So there would be vertices, there would be edges, and there would be a property graph. So when you talk about different type of operators provided by Apache graphics, you have a property operator. Now this modifies the vertex or edge properties using a user-defined map function and produces a new graph. You also have a structural operator. Now this operates on the structure of an input graph and produces a new graph. How about join operator? So join operators will basically add data to graphs and generate new graphs. So these are three important operators which are used in Apache graphics. What are the analytic programs provided in Apache Spark graphics? So there are some important analytic algorithms provided by graphics for your graph-based processing requirements. You have PageRank algorithm, you have connected components, and you have triangle counting. You can read about these more by looking into the Spark graphics documentation, where all these algorithms and what they do is explained in a very crisp and a explanative way. So what does the PageRank algorithm do? And you might have heard of PageRank algorithm, which is used by Google or some other search engines. So PageRank basically measures the importance of each vertex in a graph, assuming an edge from, say, U to V represents an endorsement of V's importance by U. Now, what we are doing here is we are looking at two different vertices. We are looking at a relationship between them, and we are looking at the overall graph, which is created by this U and V, and how V is endorsed based on U's importance. So, for example, if a Twitter user is followed by many other users, that handle will be ranked high. So we are looking at a connection where one Twitter user is followed by many other users. Now, internally, when you talk about PageRank algorithm, you can understand this by looking at or thinking about what Google does. So where you could have multiple pages which are being searched, and each page is initially assigned a rank. And based on the searches, based on the possibility of a page being found, every time the rank is incremented. Now that's how page algorithm works.
R is a popular programming language used by statisticians and machine learning enthusiasts for performing data analysis and solving business problems. Hey everyone, welcome to this full course video on R programming language. In this video, we will learn all the necessary skills that will help you master R programming. We have our experienced trainer Ajay who will take us through this full course. In this video, you will start off by learning the basics of R. First, we'll learn about variables and data types. Then, we'll look at the different R objects such as vectors, matrices, lists, and data frames. Next, we'll understand about logical operators and functions in R. Going further, you will get an idea about the data manipulation packages in R such as dplyr and tidyr. And finally, you will learn how to create different charts and graphs in R to visualize your data and draw insights. Over to Ajay now.
Hi everyone, welcome to this tutorial on R. Let's see what is R programming and how it helps. So R is well known as a language of data science. Now, if you really look at the ranking from survey of data mining experts based on the softwares they have often used in their work, R is used more than Python when it comes to data science. Python is also used, however, R is predominantly more used for data science kind of activities. It's a open source programming language used for statistical computing. It is one of the most popular programming languages today. It was inspired by S+, and it is similar to S programming language. So when it comes to data science, what we can say is R is a popularly used programming language across the globe. It is free and open source, as I mentioned. It is optimized for vector operations, which we will learn about later. It has an amazing community, has in fact 9,000 plus contributed or community packages, allowing us to do almost anything or everything using R. Now, when we talk about features of R, as I said, it's open source programming language. So you can install R for free and you can straight away start working. You wouldn't have to really go for a licensed version or pay for the software. Non-coders can also understand and perform programming in R as it is easy to understand, and it has various data structures and operators. It can be integrated with other programming languages like C, C++, Java, and Python. It consists of various inbuilt packages, a lot of sample data sets which can be used, and that makes reporting the results of an analysis easier by using R. Now, before we start learning about variables, loops, how you work with R and so on, it would be good to know how you can set up R and work on R. So for that, what you can do is you can just go to r-project.org, and once we get to the home page of our project for statistical computing, using this link, we can click on download R here. Now that brings you to a page to download it. Now there are various links here. So it shows you the comprehensive R archive network, that is CRAN mirrors, and it is available at different URLs. However, I would choose the first one, which is Zero Cloud. You can just click on this one, and then based on your operating system, whether you are working on a Linux machine, on a MacBook or Windows, you can install it. So you can just click on this one. As of now, I'm using a Windows machine, so I can click on download R for Windows, and that takes me to this link which says binaries for base distribution. Now this is what we can use to work with R straight away. However, there is one more package, that is RStudio. We will see how we can set up that. Now this one takes us to the best mirror possible for our location from where we can download R. So you can click on this base and then you can download by clicking on this link. I have already downloaded this. So once you click on this one, you can just save it. So I have it here already in my downloads, and that's more than enough. Then you can just double click and you can go through the instructions to set up R. That would also allow you to basically set up a desktop shortcut, which I have already done here on my machine. And if I go in here, I see HBase. You can click on this one, and that brings you to the page which you can use to straight away start working with R. Now, yes, there is one more package called RStudio, which is set up on top of base R, which makes working with R easier. Now, here also you can start working. So it shows you R console, and you can click on file. And if you have some scripts or files already written in the format of R, you can use those. So I can click on open script, and that takes me to a page where I have some files which are already existing. I can just select this one and click on open, and that shows me some options here. So I have an editor which shows me, say, if I want to get a library to use built-in data sets, I could summarize the data, I could do a cleanup, and we'll see all of this. But I would suggest using RStudio rather than just using base R. However, installing base R would be required, and depending on your machine configuration, like mine is a 64-bit, I have chosen 64-bit while I was setting up base R. Now when it comes to RStudio, it is basically a package which makes working with R easier. So to install RStudio, what you can do is you can go to the RStudio homepage, or you can just go to Google and say type RStudio download, and then it takes you to this page. You can click on this which says download RStudio. You can choose your version. You can go for the free version, that is RStudio desktop, and you can click on this download, and then you can download RStudio for Windows, which I have already done. And then you have to run through the steps. So just click on this one, and I already have RStudio here, right? Now I can just basically use that. So for example, if I go to downloads and if I look for RStudio, if I do a double click, I can say yes, and then it takes me to the RStudio setup. Just click on next, and here you can choose the location. If you would want to place it in a specific location, click on next, and then it says select the start menu folder. So let RStudio be chosen here, click on install, and then it will basically start installing this in a particular location. Now in my case, it is already existing, right? So we can even click on show details and see what it is doing, what packages or what executables it is extracting. Now once this is done, then you will be able to use RStudio. You can also add a shortcut to your taskbar and you can continue using it. So I've already done this. This might take a couple of seconds. Just wait for this to complete, and you would have RStudio, which is an easier way of working with R. So a lot of developers across the globe would be using RStudio when they are working with R to work on their data science or programming requirements. Now let's just wait. It is almost done, and now I can click on finish. So that part is done. You can add it as a shortcut. So RStudio has consistent commands It has unified interface. It makes easy to navigate and manage through R, and it is set up on top of your R base. Now, if I click and open on this, so that's my R Studio, which is coming up. Now, here you see console, which will show you the result where you can give your commands. So where we can get text output. Now again, I can choose a file. So I can just say open file, and then I can go into a particular location where I have downloaded some data. And then basically I can choose, say for example, R Studio, and that brings me here. So now you have your script, which has some commands, right? On the left bottom, you have console where you can see the output. On the right side, you also have environment. Now that is to use or provide variables. And then we can also have plots, which we can see here. Now we can look at this as an example. So here I am loading the built-in datasets. So what I can just do is I can place my cursor here and I can just do a control enter, and that basically loads the built-in datasets, which we can see here that has been done. Now there is an inbuilt iris data set, and we can just use head option to look at the first 6 lines of iris data set. So just place your cursor and do a control enter, and that shows you a summary, basically the first 6 lines of this data set, what it contains. We will look into this data set later. This is a default data set which you can easily find when you're working with R. You can also have your cursor placed on summary and then just do a control enter. So that basically shows you summary statistics for iris data. You can do a plot, and that basically shows you the plot, which you can also maximize and look at it in full screen. You can just do a zoom if you are interested in looking into this, and we will discuss how or what kind of information we can infer from the plots. Now when it comes to cleaning up, you can just do detach, and then we can say package data sets, and here we had loaded those data sets, so we are just doing a detach, and we can say unload equals true. So I'll just do a control enter. I can also clear off the plots by doing this for whatever plots we had, and we can either do a edit and then we can do a clear console from here, or the shortcut is control R and you can clear off the console. So that's a simple way of starting your working with R by installing R Studio. So let's continue learning about working with R. And basically the first thing which we should learn here is about variables in R. So variables, as in any programming language, is a way to store your data value, factor of list values, or a data set or object in R. It allows us to conveniently reference the variable name, basically saving us from rewriting the data value or object many times in our program. So when we talk about variables in R, they are mainly used to store data with named locations that your programs can manipulate. A variable can be a combination of letters, digits, period, and underscore. So you can have some valid variables as total, sum. You can also have dot notation. So there are different naming or style conventions in R, and we can use dot to separate names in description of a variable. We can also start a variable with dot. We can include numbers in a variable. And remember, R is case sensitive. So we have to, whenever we declare a variable, we need to remember what case was used, as in the name of the variable. And there can be other conventions also, such as using an underscore or even using a case in between the variables. So variables can only consist of letters, numbers, periods, underscores, your dot followed by a letter, not a number. And we can declare our variables. We can also look at the type of the variables and the class to which it belongs. So there are some invalid variables which we are seeing here, so that also needs to be remembered. So this is an example where you can use an assignment operator, which you see here between x and 10, to assign a value to a variable. You could also do that by doing a .y and then assign a value. You could be doing that by using a z and then having a computation done between x and y, and finally you could do a print. So let's see some example here before we move further, and for that I can bring up my RStudio here. So as I said, we can basically have different kind of variables or naming conventions. For example, I could do something like model 1 and then I can basically assign this. So this is just a variable and I could be assigning anything to it. I could be assigning different data types which are available here. For example, I could do something like this and I could do a control enter. So that's my variable. I can always do a type of, and then basically I can check what is the type of my variable. So it tells it's a character. I can also do a class, and then I can basically say show me the class, and that shows me it belongs to the character class. We'll learn about data types later, but we are using an assignment operator now. If I say what is model 1, it shows me the value, but if I would do something like this, then it says object model not found. And why? Because it is case sensitive. The variable which we had created was all in lowercase, and the one which we tried to call was starting with an uppercase. So you could have variables created in such way. I could also do something like hello underscore string, and this could be my variable where we are using an underscore, and then we can just give in something here, and that becomes my variable which you can always call and check what is the value of that. You could also be doing something like this. So you could be using different cases, and then I could say something like this, and that's also my variable. And then I can basically look at the value of this variable. Now, if we try to create a variable where we start the variable name with a number, what would happen? So if I say something like this, and then if I try to assign a value to it, for example, let's say 100. Now this one will throw an error message because you cannot have your variable starting with a number. But if I used period and then basically give something like this, and let's try doing this by giving it a number. So if you see here, since we gave a period, the rule is that it should be followed always by a letter and not a number. So I could just remove this and that works perfectly fine. So these are some naming conventions which when you practice you will learn about. So now I can assign a variable by just doing a dot pairs and then assign any value to it. But always remember, if you are using a period, if you are using a notation, then in that case that should always be followed by a letter. One more thing which is always practiced in a real-time environment is that we cannot have spaces when we are creating variables. So for example, if I say first num and then I try to assign this a value, it basically fails. But obviously I could have done this by doing an underscore, and that perfectly works fine, and you can basically then call the value for this one. Always remember, one more standard practice which is followed in real-time environment is you will try to have variable names with a little meaning to them. So for example, if I would create a variable and I would say, for example, let's say bird, that's my variable name. And then if I assign this a value tiger, it works fine, but then it really does not make sense. And that would basically create a lot of ambiguity in our coding. So it is always good to say, for example, animal, and then I would say, okay, so tiger is an animal, and that basically not only allows me to assign a value to the variable, but it is also a little bit more meaningful. Now, when we talk about variables, it is also good to know the different data types which are available in R. Now, like any other programming language, R also supports different data types. So you have your logical data types such as true and false. You have numeric values, which is say these numbers. You could also be creating an integer, which is 3L and 40L, 4L, and so on. You can have a complex number. You can have characters, which can be just letters or a set of letters or anything which is within the quotes, or you can even have raw data. So these are different data types. We can again see quick examples here on data types. Let me come out of this one. And as we saw already, when we created model 1, this was character. Now I can just say X and let's say 100, and obviously this is going to be not my integer. Okay, so let's see this. What is this one? This one by default is double. It is by default double. So if I would want an integer, then I would say, for example, something like this. And this one you can check by using type of, and you can see the value for this one. So this is an integer. So similarly, you can have character, you can have complex, you can have raw data, you can have numeric values. So all these are different data types. You could also be saying, for example, I would want to check the Boolean. So I could check this and select this one. And now when I check the value for A, it is true. And we will learn about logical operators, where we can basically be using these values assigned to the variables to compare, to compute between different variables. So this is a simple small example of using variables. So we have seen here using variables and also using the assignment operator, and then assigning values to the variables and different naming conventions. We can also be using different data types which R supports and work with the variables. Now, once we have learned about variables or data types, let's also just first learn about your operators and how they can be used in your R programming language. Now, we might be intending to do some calculations on numeric values, find out differences between values, or say, for example, compare values. So in that, we can be using different kind of operators. So we have various operators. We have arithmetic operators, we have rational operators, we also have logical operators. So before we straight away look into logical operators, let's also understand about the basics, such as your arithmetic operators, which supports, for example, let me pull up a notepad file here. And when we talk about arithmetic operators, here we are talking about your addition, you have subtraction, you have multiplication, you have division, and you have remainder or modulus, and you have exponent. And what makes it also important is that when you're using arithmetic operators, you also need to know about the order of operations. So when you say order of operations, always the priority is to parenthesis. So that takes the priority. You have then exponent or your computation if that would involve exponent. So let's say exponent here, which is then followed by your multiplication and division. And that one also follows an order of left to right. whichever comes first when we talk about multiplication and division, and similarly when we talk about addition and subtraction, it is left to right, whichever comes first. So these are some of the arithmetic operators. Now we can see some examples here quickly, although these are some simple examples. So for example, I can say 100 plus 100, and that gives me the value, right? You can always do 100 minus 50. You can do 100 multiplication. You could do 100 division too, or you could also use modulus 2, which basically gives you an error here. So I will, oh, just give me a minute. So let's give here one more percentage sign, and that basically says what would be the remainder. So if we would want to look at the ordering when we are using this arithmetic operators, we can see an example. So for example, if I say 34 plus 46 divided by 2 gives me 57. However, if I use 34 plus 46 in parentheses, which gets the priority, and then I divide, my result is different. So understanding what arithmetic operators you can use, and also the ordering in which that leads to the computation is very important. So we can use all of these arithmetic operators, and to control the ordering we can be using parentheses, or we can have our computations ordered with what kind of operation we would want, whether that would be multiplication or division, addition or subtraction. Now at any point of time I can always do a control L, and that allows me to clear my console. Let's continue our learning and let's learn about operators. So when we speak about arithmetic operators, we see that allows us to do computations, but we have also rational and logical operators which help us in doing our computations or comparing values, or sometimes finding difference between different values, whether those are group of values or whether those are individual values. So with your rational and logical operators, you can compare data values. So if we would want to see if the values match or not match, or if the values are above or below, equal to something, and so on. So when we talk about your rational operators, we basically have, in case of rational or logical operators, so we obviously have greater than, you have less than, you have greater than or equal, you have less than or equal, you have equal to, and you have not equal. These are some of your rational operators, we can say. And when you talk about your logical operators, then you have and, you have or, and you have not. So and is when it compares two values. So it returns true if both the conditions are true, else it will return a false. So for example, if I have 10 greater than 20 and 10 is less than 20, now that's not possible, and we are comparing the result of both of these. So we are checking if both the conditions are true, and that's not really true here. So we see the value as false. Now if I would have replaced this and with or, it would check even if one of the conditions is true, it would basically show me a result as true. You can also use a not operator, which takes each element of the vector and gives the opposite value. So we can be using any one of these operators, and then basically do our computations. So let's see some examples about these logical operators. Now either you could just be assigning values to your variables in check, or you could also be picking up a data set from your machine and then try to use these logical operators. So for example, if I say X has been assigned 100, Y has been assigned 200, and if I try to say X equals Y, so that already checks the value and compares and tells me that's not true, it is false. And if I would have used a not operator, for example, if I would have said something like this one, so it tells me true. So I can just check simple conditions like this. I can say, is my Y greater than X? And that tells me yes, it is true. If I say Y is greater than or equal to X, well, it would still say true, because when you are saying greater than or equal to X, so when you're saying this one, it works fine, right? Now we can also be picking up some data set, and for that what I can do is I can pick up one of the data set from my machine. So I can go in here and I have some data sets. Let's look into that, and I would be interested in taking this auction data set and loading the values here. So I'll get this path and I will come here. I can use auction as my variable name. You could have given a dot separated name. For example, I could have said auction.data if this is what you want to do, and then you can assign variable a value. So here I'll say read.csv, and I intend to pick up a file, so I give this path. And when we are working on Windows machine, we need to give a double slash. So I'll say auction.csv. Now I could give other things like header being true, what is the separator. If you would want to fill values to take care of missing values, we can look at all of those. So here I'll just add a backslash. I will add a backslash, and I will basically just do a control enter. Now I can look at the values of this by just doing a auction.data, and I can see what values it has. So it has a lot of data here. It has a lot of your data here. You could have used some other functions which we can see later, where I can choose head and I can see the first top 5 values. So we can basically assign data to the variable and continue working on this. Now we can keep it simple, so let me repeat this step, and here I will say auction as my variable name, and I'll assign this. So I can basically do also a view on auction, so auction, and then basically that shows me a tabular format of the data, which allows me to look into the data and basically understand it, and then I can use this to work on variables. So what I can do here is I can say X, and let's say assign some value to this, for which I would want to work on my data set, which is auction. Now what do I want to do here? So let's use auction, and then I can use a dollar symbol, and I can choose which column I'm interested in. So for example, let's choose bidder, and I can just give a value to this one, and let's pick up a name. So let's say tweak, and that's the name, and I can be assigning all the values to this. Or I could say I would want to use another condition, so I'll say auction dollar, and then let's take this value of bid, and let's say it is equals to 100, and then I ended up with comma, and I can try doing this. Now here it gives me a problem, because what we did was we did not use the right operator. So we will say, for example, and. So I will say X is being assigned the value of auction bidder being tweak and auction bid value being 100. So now once we do this, I can look at the value of X and that shows me the value. So this is just a simple example of using a logical operator. Now I could have just said, instead of and, I could have used or, which is basically a pipe which you have to use, and that gives you or condition. And now hit on enter, and if I now look at the values of X, it will show me a lot of values because we have given an or condition which basically matches one of the conditions. So in this way we can use logical operators and continue working and continue doing our computations. Let's learn about print formatting and how print can be used to view your data. When you talk about R uses print function to display the variables. So for example, if I have assigned number 10 to X, I can do a print X and that will show me the value of X. What we see here with 1 in square brackets, that also has a meaning, which basically means it is a vector, and we'll learn about vectors later. So R uses the paste and paste 0 functions to format strings and variables together for printing in few different ways. For example, if I would do this, which I say is print paste and then pass in 2 strings here or 2 words here, such as hello and world, that would be printed as follows. Now I could also do a print paste and then use a separator. So my print would look something like this. If I use paste 0, then that avoids any space between these 2 words, or for example these 3 words. So let's see some basic examples here when we talk about print. So for example, if I bring up my RStudio, here is an example. So X, as we say, now this is your assignment operator, which we already discussed. Now I can be assigning a value to this. So I can just place my cursor here and I can just hit on Control Enter. So value has been assigned. Now let's look at the value of X. Now I could also be doing a print X explicitly by using print function. For example, if I do similarly for message as hello, and then I can print the message by using print. Now, if for example, I do something like this, this is not going to print anything until I call the variable or I use a print function. So for example, if I do a Y, we see auto printing shows us the value, or I could do explicitly by using the print function by explicit printing. Now whenever we look at this number 1, as I mentioned, it means Y is a vector and 5 is its first element. Now you can also use operator to create integer sequences, and we'll learn about sequences or list later, but this is just a simple example. So I am creating an integer sequence of length 20. I can place my cursor here, which would start with 10 and end at 30. So let's look at this values for our sequence of integers. Now at any point of time, you can always use a class to look at the class of say X, and that shows me the classes of integers. Now looking further, when we talk about different data types, as we learned few minutes before, so R has basically 5 basic or atomic classes of objects. So you have character, numeric values, that is real numbers, you have integers, you have complex, and you have logical values. Let's spend some time in understanding some basic arithmetic operations and how you can do it using your R programming language. Now here I've opened up RStudio, and these are some basic examples such as performing arithmetic operations. Now for example, we can add two numbers, and I can just place my cursor here and press Control Enter. That shows me the addition. I can do a subtraction, I can do multiplication, division, also going for exponential power, or use modulo, which returns the remainder. Now, when we are performing operations, what we can also do is we can change the order of operations. And in this case, we are using parentheses. So I am putting in 500 into 2 in a parenthesis plus 80 divided by 2. So first it operates what is given in parenthesis, and that's why I get a result 1040. Similarly, I can change the order of operations. So here I can give 500 into and then something in the parenthesis, so that gets operated first, and hence you get result of 1500. Now we have already discussed about the assignment operator, and what we can do here is we can assign variables some value. So for example, I create a variable called selling, and then I would assign it a value. Similarly for cost, and then we can do some calculation. So we can say profit is selling minus cost. We can do that. And here I can look at the value of profit, which shows me 250. Now let's also spend some time in understanding data types in R. So we can have different types of data. So this one shows me an example of assigning a decimal value, which is part of a numeric class. So I can do this. And then if I would be interested in seeing the value of num, so I can just look at the value of num. If I would be interested in looking at the type of num, so I can do that here by just typing in type of, and then select this one and pass in your num, and it shows me the value is double. I can also look at what class it belongs to, and that shows me it is numeric. So in this way, you can not only assign values to a variable, but you can look at the class and type of it. Now here we can assign whole numbers, which are also known as integers. Now if I look at the type of this, it shows me double. So if I would want to explicitly assign an integer, I could have done, for example, let's say j, and I could have used the assignment operator, and I could have done this. And then if I look at the value of j, it shows me the value. But what we would be interested in looking at the class of j, so we can do this, and it shows me it is an integer. So explicitly, either I can assign this by using a capital L, or I could use a function called as.integer. So we'll see that later. Now we can also assign Boolean values, or basically your logicals. So here we assign true, and then we do a false, and we can look at the type of t, and that tells me it is a logical class. Now similarly, you might be interested in working on text or string values, and here we can do this by saying ch and then passing in a value. Look at the class of this, it tells me it is, the data type is character, and if you look at the type of it, it says me character. Similarly, R also supports complex data types, so we can do that too by just doing this, and look at the class of it, it tells me it is complex. And you can also pull out the length of this by, now here we are doing a length on the character. So let's look at this one, and it shows me what is the length of this. Now one of the useful functions which we usually use in R is print. Now I can simply do a print hey, and that prints whatever value is passed to print. I can assign a value to a variable and then print it. So that is also fine. You could have also, without using function, just typed y, and that also shows the value. However, sometimes using print as an explicit function can be useful. It makes your code more readable. Now here we would use an inbuilt data set, that is empty cars, and then if you would want to print the data set, that shows me the values, which shows me the car models and different other features such as mileage, cylinder, horsepower, and so on. Now, one of the use case of print with a paste function can also be seen here. So I'm doing a print paste, and that basically prints whatever was passed in a concatenated way. I could also do a print paste with a separator if I would want to format my data in a particular way. So here I've used separator as comma. There is one more function, paste 0, which can be used. So I'm doing here paste 0, and that tells me just concatenate these values without any space. So paste 0 shows no space between these two elements which were passed. Now we can explicitly do some printing, and for that I'm using a sprintf option. I am going to pass in %s, which is for string, and %f for float, and we can print the values of this. So these are some basic operations or usage of your functions to basically do some computations or look at your results. So when you talk about basic type of any R object, it is a vector. And when we talk about vectors, empty vectors can be created with vector function. A vector can contain objects of same type or a class. Now when we talk about list is a vector which contains objects of different classes. So these are some basic examples. So apart from your print formatting, we can be looking at what we call as R objects, such as vectors or lists and so on. So when we talk about vectors, it is a sequence of data elements of same basic type. We use the function to declare a vector. So we can always do a C function to declare a vector. For example, here we are creating a variable v1 and we are assigning it a vector by using C and then giving some basic types, so numbers 1 to 5, or for example words. You can always do a print, or you can also use a class to find out what is the class of the elements or the values which have been passed to the particular object. So we can look at some examples like this. For example, we can see here, so list is a vector which contains objects of different classes. So you can have numeric objects, so that is your numbers such as 1, 2, etc., which are your numeric values. For example, here what we are doing is we are assigning a value 1 to a, and that can then be used. I can either do a print or I can just use auto printing. I can also do here a value for AI, or I could be doing something like this, which shows me 0, which can be for missing value. So if I would want to use auto printing, I can just call A and it shows me the value what has been assigned to it. You can always use a type of to look at the value of A, which is double by default. And if I look at type of AI, that is basically an integer because we used L here. So in this way, we can continue working with, say, different classes of objects. So for example, let's create a vector here. So I can say v1 and then basically assign it by using a C function and then pass in the values to this one, and that basically gives me a variable, and you can look at what are the values assigned to it. Now if I look at the class of v1, that shows me it is numeric. If you use type of and then you would want to see the values of v1, that shows me the values are double. Now as we were seeing here, we can be looking at the class. So for example, if I create one more variable and then assign values to it using C, so passing in some words here. For example, let's go and say hello world, and then I can basically do this and look at the values of this one. I could also explicitly print, as we discussed earlier, by doing a print v2. We could also be having a paste function if we would want to use that. So for example, if I would do a paste function, I could be using, and this is missing a bracket, so let's complete this, and that shows me the value. I could have also used, for example, paste 0 function, and that also works fine. So it depends on what we are looking at here. So if I look at class of v1 which we had, it is numeric, and v2 is basically having elements which are of the class character. So this is just a simple example of having your print functions, having vectors created, printing out the values of those, printing out class and type of these. To continue our learning on vectors, as I mentioned earlier, we can use the C function, which can be used to create vectors of objects by concatenating things together. So for example, if we look at this one which says X, and then I use C function and I say 0.5 and 0.6, so we can have a vector of numeric types. So let's do this, and then we can look at the value of X. So it shows me my vector which has 0.5 and 0.06. I can also have my vector of logical values, and now let's look at the value of X. So it has true and false, or we could have done it in this way where we can then look at the values. So we can use the short form by using capital T and F. I can create a vector with character types and then look at the values of those. I can also be creating a sequence of integers as we saw in previous example, and then look at the values which start at 9 and end at 29. Now you can also create with complex types and look at the values. So these are some simple examples of creating vectors. Now we can also use vector function to initialize vectors. So for example, if I would do this, where I'm saying my vector will be of type numeric, length is 10, and then look at the values. So it just shows me a vector which has all zeros and the length is 10. Now you can create a vector of numbers by doing this as we saw in previous example, and use explicit printing to look at the values, or might be a letters, and then use a print statement to print function to basically look at the values of the vector. Now we can also try concatenating the above two, so that creates a mixed vector which has two different kind of types here. So I can do a mixed vector by using the C function and then passing in my numbers which has numeric types and letters which has character types, and then we can basically do a printing of this which shows me the value. But here what we see is coercion, that is basically casting, if you would know as the word in different programming languages. So it basically coerces the numbers to character, as characters cannot be coerced into numbers. And then you can print the values of this mixed vector where everything is of character types. So for example, at this point of time, if I would have done something like class of mixed vector, and if I would want to look into the values of this one, it shows me everything is of character types here. Now data type of different vectors can be returned by the function class as we saw just now. So it is common to use the class function to integrate an object asking what is the class. Now we can create one-dimensional objects such as an integer vector, which we have done earlier, and then look at the class of it, which tells me it is an integer. I can also create a numeric vector by giving in some values here. So when we do this, So I have given the vector function C and then giving in the value and look at the class, it shows me it would have numeric values. Now you can create a character vector and then basically look at the values of it. Now at any point of time in all of these, for example, if I would do num, I can see what are the values assigned to it. I can do letters and I can see the values of this. So let me just create some space here. Now I can create a factor vector and then look at the values of it, or also you can see what is the value in this factor vector. So here we said as dot factor, so factor function is being used here, and we are creating a vector of letters, and then we look at the class. We also look at the values what are assigned to this or what are in this particular vector. So if you look into all of these vector examples, initially we were using an assignment operator where we were using the C function, and when we started creating vectors by say concatenating or vectors of particular types, we are using equals here, and that also is fine. Now looking further, when we look at concatenating two different kind of vectors, so for example here we have say numbers and letters. As we discussed earlier, it will do coercion, that is change one type into other. Now when we talk about one-dimensional objects, we can have integer vectors or say float, which we saw just now, ending at 10.5. So when we say C 1:10, it basically starts with 1, but then there is also, you can say, a coercion happening here, and then you have the values ending at 10.5, that is float, and I can look at the class of it. And when we did a class of, did we do a class? Yeah, so let's come here and let's do a class of this one. It says me it is numeric. You can look at the values of it. Similarly, you can create a character vector which is 1 to 10 and then basically look at the class of it, or basically the value of this vector, or as we did the factor vector. Now for two dimensionals, we will explore that when we are learning about matrix. So as of now, let's forget that. Now when you talk about mixing objects, there are occasions when classes of R objects get mixed together. So that could be accidentally or that could be intentional. So if you look at this example here, we have Y, which has been given values which is 1.7 and A, and at this stage, if I would look at the value of Y, that's my vector. If you look at the class of Y, that shows me it is as character. Now when you look at some other examples, so let's pass in logical and numeric values. What would happen in this case? So we can again use class of Y, and that basically has numeric, and if you would want to look at the value of Y, that shows me 1 and 2 here. Let's go further. So let's look at the value of this one, so Y, and then basically see what is the value of Y. So it is A, true, and you can also look at the class of it. Now we are mixing objects of two different classes in a vector. Remember, when we talk about vector, we always talk about vector having elements of same type. But when we talk about lists, which we will learn later, that would have basically, or that can have your each element of different type. So for vectors, it is not allowed. So when different objects are mixed in a vector, coercion occurs so that every element in the vector is of the same class. Now, we have seen earlier the implicit coercion where R tries to find a way to represent all the objects or elements, as I say, so all the objects in the vector in a reasonable fashion. So we can also be doing explicit coercion, so that is from one class to another by using a as dot and then using a relevant function. So if I have x here, now if I look at the class of x, it tells me it is an integer, but I can convert that to numeric by doing a as dot numeric or as dot logical or as dot character to basically do a coercion and change the class of the objects. Now, if R cannot figure out how to coerce an object, this will result in NAs being produced, which we can also relate to missing values or not applicable values. So for example, if we create X and look at the class of X, it tells me it is character. Let's try changing character to numeric, which will not work. And it says NAs are introduced. If you do it even in logical, that would not work, and it shows me NA values, or if you do a complex, it says values have been introduced. So at this point of time, if I look at the value of X, it tells me it was assigned ABC, and we try to convert that into a different class. Now, when we talk about vectors, it is also good to know about attributes in brief. So all your R objects have attributes, that is metadata for object. So when you talk about R object attributes, you could have names, you can have dimension names, you can have the dimensions, that is matrices and arrays. You can look at the classes such as integer, numeric, and so on. And you can also look at length, which is user defined attribute. So if I say X, we are assigning a value to X. Now at this point of time, if I see my value to X is 1, but then all objects need not necessarily have attributes. So in that case, whenever you try to use an attributes function, that would return null. So at this point of time, if I look at the attributes of X, it shows me null value. So these are some of the basics which help us in working with R and using your vector function, or looking at the coercion which is implicitly happening or explicitly can be done by us by using a as dot sum function. Now let's learn about lists and how we can work using R on list. When we talk about vector, which we saw in previous examples, vector is a one-dimensional array, right? And it can hold elements only of same type. So we would say vector is more of one-dimensional. But when you talk about list, list is a generic vector that can contain objects of different types. So when you talk about, say for example, matrices, matrices can also hold elements of same type, but in matrices, it is a two-dimensional array. We will talk about matrices also, we will learn. So when you talk about lists, they can contain all kind of R objects. So you can have dates, you can have data frames, you can have vectors, and many more. So in list, there is no coercion which is required, that is changing of data type. There is no loss of functionality, and lists do not follow any predefined structure. Now we can create lists using this list function as it is shown here. So you can create a variable and then assign a list to it, where you can be using either passing in a vector, or what you can do is you can simply create a list by using this list function. So let's see some example here. Now for that, what we can do is I can bring up my R Studio, where we can see an example on list and how it works. So when you talk about list, what you can do here is, let me close this one and this one. Yeah. So what we can do is we can basically say, for example, test, and I can basically give something here. So for example, I can say music tracks, and then I can say how many hundred of them, and I can say, let's give 100 as number, and then we can say how many of them got 5 stars, and I can do this. So I can check this, and this shows me all the objects or elements of this list, right? Now, when we do this, what we are doing is we are creating a vector, right? And vector basically can have coercion depending on what are the elements which are passed, because whenever you use the C and you create a vector, it will only accept elements of the same type. So for example, if I do a class on test, it shows me here all the objects are of type character, right? And you can also use type of to check for our test variable, and it is basically having all the objects as character. Now, how would you create a list? So what we can do is we can use a list function. So for example, let's again do a test here, but this time I'm interested in creating a list, and list can have objects of different types. So let's say music tracks, and then I can just give 100, and I can say with rating 5. And now if I look at my test, it shows me all the elements of your particular list. Here we see each element or each object with a double bracket, and we can see each element. Now what we can also do is we can use is list function, and then we can pass in test here to check what is it, and it is a list, right? So here we have created a list, but if for example we take the previous example where we were creating a vector, and if I would do a is list, it would show me false, right? So we just created a simple list, and we can also arrange labels, or we can use a name function to basically give names. So what I can do here is let me create a list first. So I can do that like this. And now what I can do is I can do a name, and I can use a name function to this test. And then basically what I can do is I can pass labels. So here I can just give in some names here. So for example, I can say, let's give it a name, product. So say we are talking about product of a company, and then we can say here I can give count, and here I can give rating, and this is basically to give in names. So let's just give, there's some error here, let me just check this. So let's use this name function here, and what I'll do is I will basically use names, and now let's do a test. So that shows me the names what we have assigned to our list objects. Now we can always access the elements of or objects from a list using indices or even using double square. So for example, I have test here, and basically I can give something like this, which gives me based on the indices the position where you are accessing the elements of the list. So we can do this. What I can also do is we can specify names when creating a particular list. So for example, what I can also do is I can say product dot category, and now I can just give list function. So I would want to assign names while creating a list. So I can say, for example, product, and this would be, say, music tracks. Then I can give, say, for example, count, and count would be 100, and then ratings, and I can say 5, and Now we can basically access this list which we have created. So what we have done here, unlike earlier when we created a list and then basically used names function to assign a name to it or each object, here while creating a list itself we passed in the names. So we can also do that. Now if you would want to basically display the list or compactly display structure of a list, we can always use the string function, and here I can pass in the name. So let's choose this one, and this is in a more compact way listing down the elements of your list. So list can be containing other lists also, and we can also do that. So for example, I create one more list. For example, I can say similar product, and here I can give a list again, and what I would want to do is I would want to say product equals, and I can say film, and then I can basically give a count, and then I can give ratings, say 4. And here what I've done is I have just created one more list. But my intention is not just to create a list, but I would want to add this to our existing list. So what we can do here is we can take our previous list, that is product.category, like what we did earlier, and now I intend to say list, and here I would want to say, for example, let's copy this, or we can just, so this is what we were doing when we were creating a list using product, giving the names while creating a list. And what I also want to do is here I will just say similar and then pass in similar dot prod. So now if you look at our list, we have just added new elements. So this is one more way where we can create a list and we can basically add, or our list can have other lists. So when we talk about subsetting or extending list, so one of the main ways, as I said, to access a specific element or a subset, we use double brackets, and we can always do that. So for example, we take our prod.category, and then I would want to access a particular element. So I can always do this by giving the index positions, and I can access the elements of my list. So this is one single way. Now here, if we use a single bracket instead of double bracket, then in that case, the output would be a list. So if I look at this one, then this would be a list. But if you use double brackets, then you're accessing a particular object. If we were creating a vector, we could just be using a subset by using the C function. Now, what we can also do is we can subset by names or even logicals. So what we can do here is we can take this product category, and if we have defined names, then in that case, what I can do is I can say I would be interested in music tracks, and this is the name we had given. So we can close this one, and we can try accessing the elements here. So what's the name we had given? So no, it's not music tracks, that's the value. The name is product. So we do this, and then we can access the elements. What we can also do is we can be subsetting based on logicals. So what we can do is we can basically just give something like this, and here we can pass in values. Something like this. and we missed a bracket. So that's also a way of pulling out the values. So you can be doing a subsetting using the names which you have assigned to objects within your list, or you can say names which you have assigned to the elements, or by using logicals. Now what we can also do is we can use the dollar function. Now if you see here, we are looking at the name and that is preceded by dollar. So we can always pull out the values from our list by giving the list name and then give a dollar symbol and then choose the name. For example, if I choose product, I can list the values here. I can be looking at, say, dollar and then choose a count. And this is also one way of accessing your elements from the list using your dollar symbol. Now, to add elements to a list, as I said, you can add a vector of names and that can be passed to your list. So these are different ways in which you can work with list, and then you can access the elements either using indices or using names or even using dollar symbol and pointing the right names. So this is one simple example of working with your list. Now one more, and now I can just do a Control L and I can clear that off. So your list, always remember, is a generic vector that can contain objects of different types. Now when we talk about matrices, now matrix is a collection of data elements arranged in two-dimensional rectangular layout. So we can use matrix function to create a matrix as shown here. So matrix is two-dimensional. Now we already know that vector is one-dimensional array of data elements or a sequence of data elements, but when we talk about matrix, it's a collection of data elements that is two-dimensional, arranged in fixed number of rows and columns. So here you see that we are creating a matrix and we have specified the number of rows is 3, number of columns is 3, and we want it to be arranged by row where we have given the value as true. So always remember, matrix is two-dimensional and matrix can have only one atomic vector type, unlike your list. It's a natural extension of vector going from one dimension to two dimensions. So matrix actually needs a vector which contains values that you place in a matrix and at least one matrix dimension. So we can choose to specify the number of rows or number of columns when we are creating matrix. So let's see a quick example of working with matrix. So for example, I could just say matrix which will have values 1 to 6, and then I can basically give n row and you can give a value to this one, and that's my matrix. Similarly, you could also be giving n columns. So I can just say n col and I can choose this one and then pass in the value. So that's a matrix where R fills values column by column. Now if you intend to fill up matrix in a row wise fashion so that your values 1, 2 and 3 are in first row, then we have to just modify this in a little bit different way. So we have to say matrix 1:6 n row is 2, and then I can give by row. So you always have these helper functions which allow you to pull out the values. So for example, I do this and then I can do a Control Enter. So now if you see, you have the values 1, 2 and 3 in your first row. So when we pass a matrix function to a vector that is too short to fill up an entire matrix, then something different happens. We can have a look at this. So say you pass a vector containing value 1 to 3 to the matrix function and say explicitly you want a matrix with 2 rows and 3 columns. How do we do that? So for example, I can say matrix and here I can say 1 is to 3. Now I can give n row and then I can give the number of rows which we want is 2, and then I say n column and this one I'll say 3, So I can do this, and here what I have done is I have given the values 1 to 3. I have said number of rows is 2 and your number of columns is 3. So here R fills the matrix column by column and simply repeats the vector. Now if you want to fill using a 4-element vector in a 6-element matrix, in that case obviously R will generate a warning message. Now apart from the simple matrix function which we are seeing, you also have some functions such as rbind and cbind, which are offers when you are working with matrices. So we can use those. So for example, I could say cbind, I could say 1:3, and then I can say 1:3, and that's my cbind, that is column bind, where I'm passing the values 1 to 3 and which are stacked in columns. I can also do rbind, and similarly we can be passing in the values. So I can say rbind, and that basically arranges the values row wise. So be creating a variable, for example, let's say n, and let me create a matrix here. So I'll say matrix. Now that will contain 1 to 6, and I can say by row, and then you can give value which is true, and then I can basically say the number of rows is going to be 2, and this is also fine. So let's look at the value of n here. So you basically created a matrix with 1 to 6, you arrange them row wise, and the number of rows what you have chosen is 2. So what we can also do is we can use rbind and we can add values to it. So for example, if I want to add values 7 to 9, what I can simply do is I can do a rbind. I can say I would want to edit my n and then pass in the values. So I can just do this, and this has basically appended or added values to existing matrix. So similarly, you could have done a column bind and you could have added values to your existing matrix. So for example, if I take this one and look at my n, and what I could do is I could do a cbind, and then I can basically take my n and then pass in values to this one. So let's say 10 and 11, and basically I've added 10 and 11 as a column to my existing matrix. So this is one simple way where you work with a matrix and you are appending the values either at a row level or at a column level. So let's also look at some other examples. So basically, if you would want to work with matrix, one of the useful things would be naming the matrix. That is, in case of matrices, we can assign names to either the columns or the rows. If you don't do it, we see the default values here, which follows a numbering. But what we can also do is we can use two functions here. One is row names, or you can use column names. So these are the two functions which can be used. So for example, let's do a control L. Let's try to get our n, and this is what we are doing here. But what we would want to do is we would want to give them some names. So for example, I'll say row names, and then I will basically pass in a vector which has row names or vector which has column names. So what I can do here is I can say I would want to give row names to n, and then I basically give some value. So for example, let's say row 1, and then let's say row 2, and now I can look at my n which has the row names assigned to my rows. Similarly, I could have also given column names. So all I need to do here is I need to say column 1, and then I will say column 2, and then I can be using column names. And let's look at this one. So what went wrong here? So we have 3 columns here. We forgot that. So we have to add one more column name, and then it should be fine. So now if you look at this one, we have just given row names and column names. So naming the columns or rows in your matrices can be very useful. Now, as the previous error says, there is also a function called dim names, and that's basically an argument of matrix function which can be used. So we could also do something like this. So for example, I have dim names. So let's have our n, and then what you can do is you can do a dim names, which you can then just create a list, and in this one you can pass in a vector for row 1 and then vector for row 2. And what we can do here is, once we have given this, let's give a comma here and then give C and then give your column names, which is column 1, column 2, and then basically column 3. And now if you just look at dim names, so you can just see that you have given some row names and column names, and this can be used basically to assign to your list. So if you try to store different objects in a matrix, what would happen? Coercion would take place, right? So for example, if I have X and let's basically try to create a matrix which will have 1 to 8, and let's say the number of columns is going to be 2. So let's look at our X, and this has the values. Now what if I create, say, L, and then basically I will create a matrix which will be a matrix of letters. So let's say letters, and then here with letters I'll say 1:6. Now I would want to give the number of rows, and let's give it say 4, and let's say number of columns, and let's give it 3. And now let's look at the value of L. So it has letters and X is having numbers. And what if we bind them together using cbind, which is for column wise binding? So for example, if I do a cbind and then pass in my X comma L, so if you see here, there is a coercion which has happened where everything is converted into characters. So you can always do a class and you can check. So this is a simple example of working with matrices. There are much more. You can do subsetting like what we saw in list, but that we can learn later. Now let's learn about data frames and what is a data frame and how do you use R to work with data frame. Now data frame is used to store the data in the form of a table, and for this we have a function data.frame to create a data frame. So what we know already is that data sets are comprised of observations, or what we call as instances or variables, and we always have observations to which some variables are associated. For example, we can talk about data sets of say 5 people. Now let's look at the information here. Here we look at the body mass index, BMI, where we are using a data.frame function, and then we are passing in say gender. So we use the C function to pass in the values, and then you have height, and then you have weight and age, and these things then become the columns of your data frame. So for example, if we would want to work on creating a data frame for people where let's say each person is an instance, and properties about each person such as name, age, child, or if the person has a child, would become the variables. So if we have such kind of information, we cannot easily store that in matrix or list. Now data frames can be used for such cases. Now it's a fundamental data structure to store data sets, pretty similar to matrix as it has rows and columns. And here rows correspond to observations. Now here we can talk about an every individual or every person. columns correspond to variables, that is properties for each person. Now, difference between your data frame and matrix is that data frames can contain elements of different data types. So for example, we can have one column being character, other being numeric, and yet another being logical or numeric. So restriction is that elements in one column should be of the same data type. Now, how do we work with data frames? Let's see some examples. So what we can do is we can bring up our R. So when we talk about data frames, usually we don't create data frames by ourselves. We import data from data sources such as CSV file or RDBMS or even your Excel or SPSS, and then we create data frames. Now, of course, R has ways to manually create data frames using data.frame function. So we can create 3 vectors first, and then we can pass in those vectors to create our data frame. So let's do that. So let's say name, and here I will use the assignment operator, which we have learned earlier, and then I'll use C, and then I can give some names here. So let's say John, and let's say Peter, let's say Patrick, and let's say Julie, and let's also give one more name. So let's say Bob. So this is the vector which we are creating, and we can check this is the vector which we have created. Now obviously you can do a class and you can check what is this, and that says it is a vector of character. Now similarly we can create one more vector which is age, and let's give some numbers here. So for example, let's say 28 and 30, 31, 38, 35, and these are the values for the age. So age is also created. Similarly, we can say if each person has children, so we can say children, and then I'll create one more vector, and here I'll give values which are logicals. I'm not going to give any numerics or character, but I'm using logicals here. So if a particular person has children or no. So let's have this vector created. And now we have 3 vectors, that is name, age, and children, and we can use this to create our data frame. So we can just call our data frame as df, and what we can do is we can use data dot frame function, and then what we can do is we can pass our vectors within this such as name, age, children, and that should create my data frame. Let's have a look at this, and this shows me that the data frame is created. Now column names are inferred from variables which are passed to data.frame function. So the variables which we have passed to our data.frame function is name, age, and children, and those become the column headings for my data frame. Now what we could have also done is we could have created it in a different way. So I could have said df, and then I could have used my data.frame function, and in data.frame function I could have said name is going to be name, age would be age, and then I could say children could be children, and I could do this. And this is also one more way where I'm creating a data frame, and in this way we can now have rows of data frames like in matrix. So this is also one way of creating a data frame. To look into the data frame structure, we can always use str, and then we can pass our data frame, and this basically prints out similar to that of list. So we also need to know that under the hood data frame is a list, and in this case this is a list with 3 elements. So each list element is a vector of length 5 corresponding to the number of observations. If we create data frame with vectors not of same length, we would get an error. Now here, when we look at our data frame, we know that name is a column. So name column, which is character, is actually a factor instead of character. To suppress this behavior, we can always use a property that is strings as factors equals false. So what I can do is I can do a data frame like this, use my data.frame function, and then basically we can pass in our vectors, that is name, age, and children. And then what I can do is I can say strings as factors and set this value to false. So if I do this, and now if I look at my data frame structure, sorry, yeah, now let's look at this one, and this one shows me that unlike your earlier one, now we are creating a data frame where our name would be containing characters. Earlier also by default it was showing as character. Usually because this value by default is set to false, or it would have created characters or factors, as we say. Now how do we do a subset and extend and sort data frames in R? So as we have learned so far in brief about your data frames, so data frame is somewhere like an intersection between matrices and lists. So if you would want to subset a data frame, we can always use the square brackets, and in that we can use the single square brackets which are from matrices, or we can use double square brackets from list, or we can also use the dollar symbol. So that all these things can be used to subset a data frame. So let's use our data frame which contains information about people. So we can select single element from our data frame. So here what we can do is we can just say df, and then I can use a single bracket, and I can just do a 3, 2. So it would be good if we can first print the data frame, and that's my value. And now let's do a single bracket, and let's look at this one. So this tells me that we are using the row index first, which is number 3, which shows me that we would be going to the row number 3, and then we point or pass in our column index, that is number 2. So we could have done it in a different way also. So we could have done df and then give a row index and then give the column name which you are interested in looking at, and that also gives me the value. So just like matrices, we can choose to omit one of two indices to end up with entire row or entire column. And for example, if we would be interested in looking for information for Patrick, what I could have done is I could have just done df3 comma, and this is showing me the entire row. Now always remember, whatever results we see here, that is giving me a data frame with a single observation, because there has to be a way to store different data types, and that's why the result is also a data frame. What we can also do is to get entire age column, we can just use our data frame, and then we can pass in the column name here like this, and that gives me just the column. Now here the point to notice is result is a vector because columns contain elements of the same type. In previous example we were seeing a row, and in that row was not a vector, it was a data frame because values were of different data types. Now subsetting a data frame that results in a data frame and contains multiple observations can also be done by doing something like this. For example, I will do df, and then I will say let me get 3, 5, and then I can just say age and children, for example. So let's say age and children, and I can be pulling out the values in this way. So I could also be just getting the results in the age column if I'm interested in by just saying df, and here I can just pass in the column number, and that also gives me the age column. Now we know data frame is a list containing vectors of same length. This means we can use list syntax to select elements also. And what we can do is we can use our dollar symbol and then choose the column name. And this is also one way wherein you can pull out the values, or you can use double brackets as I mentioned earlier and pass in the column name. So that's also fine. Or you can give a column number, and that also would work. And in all these cases, result is a vector. Now with single brackets, you can still do it. Always remember, if you use single brackets, then that will result in a data frame. The result can be a data frame here, but what we are seeing here is a list which contains only age column having the data elements. So these are different ways in which you can do a subsetting of a data frame. Now using single brackets or double brackets can have serious consequences. So we need to always think about what we are dealing with and how are we handling it. Now what we can also do is we can extend our data frames. That is, we can add variables, we can add columns, that is adding variables, or we can add rows which are nothing but observations. So adding columns is like adding new elements to the list, and for which we can obviously use dollar or double brackets. Say for example, now this is my data frame, and if we would want to add height whose information is in a vector, so let's say height, let's create a vector here, and this one is what I would want to add for each person. So let me do this and let me pass in some values here, and the last one something like this. So this is a vector created. Now what I can do is, so our data frame is called df, so we can say df dollar height, and then I will pass in this vector here. And now if I look at my data frame, you see the fourth column has been added, and that's my height column. Now what I can do is, I could have done it in a different way. Basically, if I had my data frame, I could have just done df double brackets and then give it a name, and then I could have passed my vector in this way. However, so this is also one way of doing it. We have already added the column, so we don't need to repeat the step. Now what we can also do is we can use a cbind function. And if you remember cbind, that is for column binding. So for example, let's create a weight vector now, and let's pass in some values here. So for example, let's say 75, 65, 54, 34, 78. And these are my values of weight. Now what I can do is I can just do a cbind and then pass in my data frame and then pass in this vector. And in this way, I'm just adding columns, or I'm extending my data frames by adding more columns to it. Now, obviously, if we can use cbind, then we can also use rbind to add new rows. So for rbind, creating a new vector won't work, because we need to create a new data frame with one single observation. Remember, row will have values of different data types, so we cannot create a vector. We have to create a new data frame, and then we can add it using rbind. So let me create a data frame here. For example, let's call data frame as Tom, and let's pass in some values here. So I will say data.frame function, and then let's give name. What we can do is we can give age, then we can give the logical value, then we can give, say, height, and since we have added weight, let's also add weight. And this is my data frame. Now we can use rbind function. So I can say rbind, and then I can pass in my data frame and this new data frame which we have created, and this tells me that the number of columns of arguments do not match. So we will have to check this one. So we have our data frame which has just height, so it does not have the weight. That was only as the result of cbind. So let's create this DOM again without weight, and now let's do a rbind, and let's again check what is the reason here. So this is height, and let me just check this. So to look at this, this is the error we were getting because I was creating a data frame with 4 columns, and then I was trying to add that to a data frame which had 3 columns. Now, yes, we had done a cbind, and cbind was showing us the 4th or 5th column, but the original data frame only had 3 columns. So what I did here was I did Tom, and then basically I created a data frame with 3 columns which matches with my original data frame which had 3 columns, and then I could use rbind to basically add one more row. So what we did was we used rbind, and rbind was used to add a new row to our data frame. Now, when it comes to sorting or ordering your data frame, say for example, we want to sort data frame by age. Now, how do we do that? So we could easily do sort df and then select our column, and we could just do a sorting. Now, if we do this, it is good, but not really what we need. Now, other clear way of doing that would be using ranks. So for example, if I do a ranks, and instead of doing a sort, I would use order and then basically pass in my column. So I would say df, and then I would use age. Now in this case, if I look at ranks, it shows me a vector of ranks with rank position of each element. Now if I do a df $age, it shows me the values, and if you look at the ranks, it will tell 21, or here the lowest value is your 28, and that's the lowest value, and that's why we see as rank as 1, and so on. We can look at the ranks. So what we can also do is we can just do a df and then basically use ranks, and we can just look at the result. So this shows data frame which is a ordered data frame now based on ranks. Now if we would want to do it in a descending order, what we could also do is we could do a df and then use order, and within order I will basically pass my data frame. I will choose my column, and then I could say decreasing equals true, and I could do this, and here this could show me the value. So it says undefined column names. So what I would have to check is what is my data frame here. So we have age, and then what we would have to do is we would have to select a particular column. So let's do that, and here I have just selected the column, and then there is a comma missing that was showing an error. So now we can have the data ordered in a descending way. So there are dozens of packages such as dplyr, data table, which can help you manipulate, filter, merge, and sort your data frames. So this is in brief about the data frames, working with data frames, subsetting them, and also sorting the data in your data frames. Now, one more important type of object in your R is vector, and that really helps us in various ways. So let's see how we work on vectors here. So to create a vector, we can use the C function and pass in the values. Those will be the objects or elements within the vector. And then you can look at the value of the vector, or also at the class of it, which tells me the values are numeric. Now in case of vector, all the values have to be of the same type or belong to the same class, we can say. So here we are creating a vector, looking at the value of it, and then looking at the class which says the values passed in here are character. Similarly, we can do it for numerics, that is true, false, and then look at the value of this, and this class is logical. Now what we can also do is we can print all the three vectors at once, and here we will use semicolon to separate two or more variables, and we can pull out the values of all the vectors which we see here. Now what happens if we pass in the values which belong to different classes, or you can say different data types? So within a vector, if you do that, there is something called as coercion which takes place, which will convert all the values into one type, and in this case it has converted everything into character. Similarly, we can pass in values wherein we can pass logical and numeric, and in this case it's not going to go for character, it is going to convert everything into numeric. Now if I had done this where I passed a character and numeric, and if you look at this, then it has converted everything into character. So character always takes a precedence if it is one of the values of vector, and you have other values which are not characters, then in that case coercion will happen. There is one more way of creating a vector, and that is by providing a range to your C function. So we can do that here, wherein I said C1:20, and then basically look at the value of vector 7. So it shows me all the values starting from 1 till 20. However, there is one more way. You can use the sequence function to do the same thing. Now I could avoid the bracket, I could avoid the C function, and I can straight away pass a range, and that is also fine to create our vector starting from 1 ending at 25. So what if I want to create a vector with odd values between 1 to 20? Now in this case, I am going to say how many values to skip or to jump. So I'm creating a variable called odd value. I'm using sequence function, and then to that I'm passing the beginning number, the ending number, and then the skip or the jump. And now if you look at the values, it shows me only the odd values. Well, we could have done the same thing to get even values, and that's not very complicated. So you can start from 2, and then you can do skip, wherein after 2 it basically gives you every second value. So we are looking at the even values, and this is how you can create a vector which is having odd or even values. Now what if you want to create a vector with 10 odd values starting from 10? So you are basically giving a length. So here you can say from where you would want to start, what is your skip, and then the length of the vector, which tells me it gives me 10 odd values beginning from 20, or from 20 onwards, that is we take it from 21. Now one of the requirements is always to name the values so that we can access the values either by indexing or by their name which have been passed to the value. So let's see that. So let's create a vector which is called temperature. So variable is temperature, pass in the values to this, look at the values of temperature. Now what we would want to do is we would want to assign these names to each value, which makes it more readable, more accessible. So I can use the names function, pass in my temperature as a vector to names function, and then assign the names to each value of temperature. Now if you look at temperature, it shows me the names which have been assigned. Well, we could have done it in a different way. We could have created a vector of names, something like this, and then what I could have done is I could have created one more vector such as temperature, and instead of assigning values, we could have assigned the vector to our existing vector. So if you do this, so you're assigning the names vector to the temperature one, and now look at the values, it still does the same thing. So this is where you are assigning names to every value of your existing vector. Now there is one more way, and that is using your sequence. So here I'm creating a sequence which starts with 100, ends at 2020 with a skip of 20 values, or every jump would be 20 values. So let's do that. Use your names function on price, and then what I'm going to do is I'm going to use my paste 0 option, which takes P, and then 1 to 7 as the values. So we know base 0 basically skips the space, and we are going to assign those values to as names to price. And now let's look at our price. So that basically gives me the names as we desire. So these are some smarter ways of assigning names to every element or every object within your vector. Now, how do we perform some basic operations? Let's have a look. So let's create a vector passing in the values, and then you can simply do an addition on two vectors where each element is getting added to other element of the vector. You can subtract two vectors, that is element to element subtraction, element to element multiplication or division, and you can basically perform operations on the vectors. Now, how do we use some inbuilt basic math functions? And that's pretty easy. This is my vector. Now let's do a sum which sums up all the elements. Let's find out a standard deviation for all the values. Let's find out the variance for all the values here. Let's do a product of vector values, find the maximum or find the minimum value. So these are some basic inbuilt math functions which sometimes are useful in our data science or data analysis kind of activities. Now, one more requirement might be comparing the vectors using comparison operators. And this is where I create a vector 1, create a vector 2, and let's find out the values in V1 which are smaller than V2 values, and that gives me the logicals as the response, that is false, true, and false. Similarly, you can do V1 greater than V2, or you can say where V1 values are not equal to V2 or equal to V2. So these are some simple comparison examples. Now I can create a different vector, and then I can find out individually if the elements in the vector are lesser than 3 by just doing a V lesser than 3. So it compares each element with this. So you are actually using one scalar value to compare it with all the elements, and you can do that. It gives you the logicals. So you can also be doing slicing and indexing on vectors. And this is very much important when you're storing your data in vectors. How do you access them? So let's create a vector using sequence. Let's give it some names as we have seen in past. And let's look at our price 1. So that tells me the name and the values. Now you can access the elements using indexing. So let's get the third element, and it shows me 590. Remember, the indexing here starts with 1, unlike other programming languages like Python, where indexing starts with 0. Now I can also get the third and fourth value by doing a 3:4. I can also specify the vector and say 1, 4, and that shows me the first and the fourth position, or second or sixth position. So this is one way where you are using indexing to access the elements. Similarly, I can give the names. Now that's where we see the benefit of giving names to every element. So I can use C function, pass in the name, and look at the value for that particular name, or selectively select different columns or different names. Or we can also use this square brackets wherein we pass the names. So sometimes it can also be useful to use logical positioning. That is, we would want to find out the logical position if the value exists, and we can do that, or using true and false and then look at the values. So there is one useful way where you can exclude a particular position. Might be that is an NA value, might be a value which you are not interested in, and that's where you will say -2, which will skip the P2 value, or -2 and -5, where we are skipping a P2 and P5, and we can exclude particular values from our vector. Now, how do we do a comparison operator on the values of vector? So you can just say price 1, and I would want all the values which are greater than 600, or you can assign this to a filter and then basically pass in the filter for your vector. So these are some simple basic operations which you can run using your R programming, where you would want to manipulate, where you would want to store some data and extract that data, use your different logical operators or other operators and perform your basic easy computations. Now that we have seen some basic operations using R, let's look at some more operations when you're working with vectors, such as one of the common issues is handling the missing values. Now here we are assigning a vector to a variable order detail, and this one has a missing value. Now let's see how this is handled. And you see all the values in the vector are assigned. What you can also do is you can assign names, as we have seen earlier, by using the names function, and then look at the value of order detail. So you see the names, and these are your missing values which are also taken care. Now what we can also do is we can perform an operation on a particular vector which will be applied to all values of the vector. So for example, here I will just add a scalar value plus 5 to the elements in the vector, and that shows me number 5 has been added to each element or each object in the vector. Now, if you would want to work on two vectors, for example, to add two vectors, let's create a vector called new order, and then let's add it to order detail. Now, in this case, what we are doing is we have a vector which is from 5 to 10, and what we are doing is we are adding values to order detail. Now, our order detail earlier was 10, 20, 30, NA, 50, and 60. And what I have done is I have passed in a vector which is 5 and 10, and you're adding it to the elements. So 5 gets added to 10, and then your value 10 gets added to 20, and then you have again 5 which is added to 30. Now you cannot add in anything to a missing value, so that remains as it is. Then you add again 5 to 50, and then 10 is added to 60. So in this way you are adding two vectors which are not of same length, but you are adding these values. Now what I can also do is I can update the order by doing this. So I'm creating an update order, and now let's look at the value of update order. What does it show? So you are basically doing the same thing. So if you would want to work on a subset of vector, how do you do that? So here you are using some indexes. So I'm saying order detail, and this is my order detail. So let's take 1:2 and assign it to first two. So if we look at the value which is assigned to first two, we have just sliced and added a subset of vector to this one. And if I would want to take the length of order detail, it shows me the length here, which is 6 elements here, including the missing value also. What we can also do is we can do some more operations. So for example, from order detail, what I'm doing is I'm saying length minus 1, and then up to the length. So let's do this, and let's see the result of this. So what we have done is we had our order detail which had these values, and what we have done is we have said length minus 1 colon length. So you have taken these two elements and you have assigned that to your v1. Similarly, we can do length minus 1 and 2 elements. So I can do this, and now let's look at the value of v2. So this shows me the value where you are taking length minus 1, and then you are taking it till the second position of the index element, which is 20. So you are getting in the values here. So you get your 50, NA, 30, and 20 because you started with length minus 2 and up till the second index position. Similarly, we can use the length and we can take it from this element, and let's look at the value of v3. So that shows me that I'm doing some slicing, or I'm getting subset of my vector. So similarly, you can also do this one. So v4, and let's do this, and then let's look at the value of v4. So it gives me the values based on our subsetting or slicing. Now you can extract all the values below 30, and this is where you are doing a comparison So you will take your vector and then you would want to compare each value if it is less than 30, and you would want to take all the values here. So it gives me the logicals or the response for all the values which are lesser than 30. What we can do is we can also use the square brackets and do this. This will show me the actual values. Here we were just getting the logicals, but here we are getting the values. Now to omit NA value from the vector, we can use NA.omit, and this one will help me in getting rid of the NA values. Plus I'm also checking the values if they are less than 30, and then I am basically doing using this NA.omit. So you can do something like this. You can look at the values. What you can also do is you can find the order details that are multiples of 3, and here we would want to use modulus, and we would want to find out if the remainder is 0, then I'm getting the numbers which are divisible or multiples of 3. So let's do this, and it gives me again the logical values of all the values which are divisible by 3, giving us a remainder of 0. Or if you would want to look at the values, then you can say order detail, open up a square bracket, and then pass in your condition. Now we can then omit NA from this one, and then we can look at the values. So this is a simple way where you are subsetting a vector or extracting the values which you are interested in, which might be one of the requirements of your data wrangling or data manipulation or just data extraction. Now I can also use a sum function. Now if we do this, it returns NA because there is already a missing value and you cannot do a sum on the values. Now what I can do is I can do a NA.rm to remove the NA values. So I can do a sum on order detail where I intend to add up all the values. But what I also want to do is I want to remove the NA value. So I'm giving it a value as true. And then if I do it, it gives me the sum of all the values. So similarly, you can do a mean, you can do a maximum, you can find out the minimum value, standard deviation, or even square root. Now these are some simple operations what we are doing on vector, where we are interested in extracting some specific values. Now let's look at matrix, which we have also discussed, and matrix is also one way where you can use the matrix function to create a matrix which is multidimensional. So for example, if I do this and if I look at the value of V, I get a matrix which starts with the value of 20, ends with 30, and at any point of time you can convert this to matrix. So first we created a vector, and now I'll create a matrix out of it, wherein I am seeing the row numbers, I'm seeing the column number, and I'm seeing the values in that particular column. So you have already done that. Now let's take it to the next level. So let's create a matrix wherein we are using the matrix function. We will say 0, 3, 3, and now let's look what it has done. So you have created a matrix which is of 3 columns and 3 rows, and by default the row number and column numbers have been assigned to them. We can also create a matrix by passing in values. So we can say 1:9 and then give the dimensions, that is number of columns is 3, number of rows is 3. And if I look at the matrix, now I have passed in the values to my matrix. So sometimes you may want to arrange the data in a matrix for particular kind of calculations. You can also use n row and by row. So you can say how many number of rows you would want, and you would want to assign the data row wise. So when we are doing this, now if you notice the difference between the previous one where we just gave the values and we said 3 rows and 3 columns, so it was doing it column wise, so 1 2 3 4 5 6 7 8 9, but here we said by row is true, so it has arranged the values in a row wise fashion. So it goes 1 2 3 4 5 6 and 7 8 9. Similarly, I could have just done this by giving the dimension and selecting by row, and if I do this, it is still doing the same thing. Now What we can also do is we can create matrix using vectors. So here, let's create a vector stock1 and then stock2. Now, we would want to merge both the vectors. So you can always do a C function and then create a new vector that is stocks, which is a merged result of stock1 and stock2. And let's look at the result. So that's my stocks, that's a vector. And now what I would want to do is I would want to create a matrix using this stocks. So I'm giving it a name, that is stock.matrix. I'm using the matrix function wherein I will pass my vector. I will say by row. So I want the values to be arranged row wise. And I'm also selecting the number of rows. So if you look at this one, so the values which we had in our stock, which was all the values, have now been arranged row wise and in 2 rows. So it starts with 450, 51, 52, 45, and 68. That's my first row. And the rest 5 values are arranged in the second row. So one of the main requirements is instead of going for default column names and default row names, we can give specific names to our columns and rows to make more sense to the data. How do we do that? So we can basically say days. So this is a vector which we are creating. And then what we want to do is we want to create a new variable, which is stock1 and stock2. Now, this is for my columns and this will be for my rows. Now, how do we assign that? So we can say column names, and this is where I will say on my stock.matrix, I will assign days, which has 5 values, and that will become my column names. And similarly, using row names function, I can basically assign row names to my matrix. So if I look at my matrix now, it shows me the column names and row names which we have assigned or which we have passed to our matrix. Now, there are different functions which are associated with the matrix, and let's look at some examples. So these are some simple basic examples. Now, if I say, let me find out the number of rows, and that gives me the number of rows or number of columns, or get a dimension, that is the number of rows and columns of your matrix. Now, we might be just interested in getting the row names or column names or even the dimension names, which basically will give me, returns the row and column names. So in this way, you can use these simple functions which are associated with matrix to extract information about your matrix or data which has been transformed into matrix to pull out some information about that. One of the requirements which data scientist or data analyst might face is carrying out arithmetic operations on your matrix. Now what we can do is we can create a matrix which takes values 1 to 50. We want to arrange it by rows, and we will say number of rows is 5. So that's my values starting from 1. Now I can do a addition here by just doing a 5 plus mat1. And if you notice, number 5 as a scalar value has been added to every element of the matrix. Similarly, you can do a multiplication, you can do a division, you can basically return the quotient if you would want to do that, or go for exponential values. So you can perform simple arithmetic operations for every element of the matrix. And what if you want to have arithmetic operations done on multiple matrix? So let's create mat1 plus mat1, and we get a total where every element is added to every element. You can do a subtraction, you can do a multiplication, and you can get the value. So this might be also very useful when you're working on multi-dimensional data. You can also do some more operations on matrix, such as returns the sum for each column. Say you are doing a summation or at a row level, or you want to do a mean for every row, you can do that by using these simple functions. Now you can add rows and columns to a matrix using rbind and cbind functions. So rbind is for row bind and cbind is for column bind. But for that, we have to first create a vector. So let me create a vector of same length, which will then be added to every or added as a row to my existing matrix. Now my matrix has 5 columns. So let's create a vector with 5 elements. And then I can basically add this as a row to my existing matrix by doing this. And now if I look at my values, I will see the new values as the third row. And if you also see, the variable name becomes the row name, and we have added a row to our matrix. Now similarly, I can find out row means, that is, we have seen earlier by calculating the mean or average. So I can do that, and I can find out the value of average. Now what I can do is I have got the average for every column, and what we can do is we can basically do a column bind by using a cbind function. And I will say I'm going to take the total stock, which has 3 rows, and then get the average. And now let's look at the total stock, which shows me the average value, which is the new column which has been added to the matrix. So these are some simple, very simple operations which you can do, but that gives you good insight in what can be done at a matrix level where your data is arranged in multi dimensions. Now, how do we do a selection and indexing in matrix? So in vectors, we were using either names, or we were using positions, or we were using indexing. Now here, let's create a matrix called student, and we are using the matrix function. But within the matrix function, we are using the C function to create a vector, which will pass in all the values, which also has NA values if you closely notice. We will split these values into number of rows is 4. So that means the number of values in this vector should be a multiple of 4. I'm saying columns is 4, and I would want to arrange this data row wise. So I've done that. And if you would want to get the dimensions out of this, so I can do a dim names. So what I'm doing here is on my student, I'm assigning a list which will basically have these names which are basically assigned. And now if you look at your student, it basically shows me the values which were first applied to the row names, that is John, Matthew, Sam, and Alice. And then you have one more vector which goes as the column names for the values. So you have not only created a matrix by using a vector, by defining your dimensions, that is number of rows and columns, you have arranged the data in a row order. And what you have also done is using a list function, you have passed in the values which will be applied as row names and column names to your matrix. Now, how do we extract particular columns here? So we can take our matrix and we can just say comma 1, and that basically gives me the values for John, Matthew, Sam, and Alice. And what we are looking at is the first column. Now I can also say from first column onwards, I would want to look at how many columns. So I can do this. And now here I'm selecting first and second column. I can also be using a vector function here, and that also does the same thing where I'm saying 1, 3, and I'm getting the values from first and second column. So third is not included here. Now, if you would want to do row wise, then you have to give the row position first. So if I do a student 1, that gives me the row values. And this is giving me values for my student, which we are seeing here. So for John, we have 20, 30, NA, and 70. And that's what we get here when you do a row wise operation. You can also do a row wise and how many rows do you want. You can use the vector function to do that. You can also select or slice out a value where you are getting an intersection of row 2 and column 2. And then you can also start from a particular position and then onwards get your rows. So these are different ways in which you are slicing the values from your matrix by columns or by rows. So at this point of time, let me just type in student here and let's look at the value of student. And then here we are interested in 3:4 and then 2:3. So what does that give me? So you are looking at third to fourth row. So you're looking at Sam and Alice, and then you are looking at columns 2 and 3. So that basically gives you your 26, 32, 24, and A. So first is you're giving your row positions or how many rows you want, and then you're giving your column. So similarly, you can do this. You can say from row number 2 to 4, and then column wise, you can say 1 to 3. So if we do this, so this tells me 2 columns, which is first and second, and it shows me rows, which is from second to fourth. So in this way, we can extract data based on rows and columns. Now, if we would be interested in finding out a specific value, so for example, if I again bring up student, this is my student, and what I would be interested in is getting the value of John and for specific subjects. So might be we are looking for 2:3. Now if I do this, it shows me for John, and what we are interested in is 2:3. So that gives me the value for chemistry and biology. So you are giving the columns. So row wise, you have already specified the name, and that basically selects the particular row. I could have given a number and chosen which row or which rows we would want to pull out the values. Now, if I would want to find out the value for John and Sam, now in that case, I could use indexing or positioning, but that has to be continuous. But here you're talking about John and Sam, which has Matthew in between. So we will basically we will get the values for John and Sam, and then we will look at the value for. Now that is basically giving me the values in the fourth column, which is 70 and 75. Similarly, if you go further, you can look at maths and bio score of Sam and Alice. So you will give your row names, that is Sam and Alice, and then you would want the values for maths and bio. So that is basically your third and fourth column, and we can do that by looking at the values. How do you find out an average? Well, that's pretty simple. You can use the mean function on student. You will select your row name, that is John. You also want to get rid of NA values, otherwise that will give a problem. So you get rid of that by saying NA.rm equals true, and then you get the average score of John. Now, how do I do further computation? That is, if I want to find out the average and total score of all students. So in this case, I can apply, or I can use an apply function. Here, I'm saying I'm working on student, and we would want to give the row number, that is 1, and we want to also give the column. So I want to find out mean. I want to remove or get rid of the NA values. And now if I look at help apply, it tells me how does the apply function works over array margins. So I will do an apply function on student, where I would want to select the first row. I would say I want the sum, and I want to get rid of the NA values. So this gives me the sum for each student. And here we are getting a mean value, which was for each student. So what we are doing here is, for example, let's look at student again, just so that we avoid confusion. So we have student, and then we have physics, chemistry, bio, maths, and I have said row 1. So basically what we want is, for John, we want the total. And what we can do here is we can say 20 plus 30, avoiding NA, and then 70, that gives me 120. Then you look at Matthew. So this is again doing a totaling. There is no NA value, and you look at the value, right? So when we have chosen apply function, we have worked on student. Now here we are interested in the values, that is sum of all the values for this particular row. I'm saying take care of NA and then give me a sum. Similarly, you did a mean, and that was giving you a mean for each student. So these are some simple operations. Now what we can also do is we can basically create a vector called passing score. And what we would want to do is we want to get the values or find in how many subjects Alice has passed. How do we do that? We will have to compare Alice score, which should be greater than or equal to the passing score. So what we can do is we can create a variable here, pass. Now I'm saying student. I would be interested in the values for Alice. So I've mentioned that row name here. I'm then comparing it with passing score, which we have created here, and that will give me the values wherever Alice has passed in a particular subject. Now I can obviously get rid of the NA values and then look at this, which basically tells me there was one subject in which Alice passed and rest were either false or NA. Now same thing we can do for Sam. So Sam is here, and what we want to do is we want to look at the values here. So we will say let's do the same thing for Sam and find out the comparison with passing score and get rid of NA values. So you are basically extracting values. So these are some easier operations and usage of functions on your matrices, which are filled in with values at row level and column level, and then you can apply one of these functions or multiple functions to basically extract value, which makes more meaning. So that's with your matrix. Now let's also look at data frames. Now data frames, as we know, is basically data which has been ordered in rows and columns, wherein we can assign row names, we can assign column names, we can do some operations on data frames. So let's look at example. So if I do a data here, so that gets me some sample data sets or functions what we have here. So let's do, once we have our data here, so it says use data package, and then you can get list all the data sets in available packages, and you can basically look at all the R data sets which we are seeing here. It has opened up. So I would be interested in getting the air passengers data. So I'm going to pass that in the data function, and then if I do a head to see the initial data from air passengers, it shows me the values what we have. Similarly, we can do that on iris data set and look at the head values. I can do a view to look at specific values in a tabular format if that makes more meaning and that makes it easy for analysis. Now I can do a view on state X77, and that basically shows me the population and income and all this for different US states. So these are some different data sets what we have. You can do a view on them to basically understand the data or look in a more readable format. You can just do a tail to get some end data. So head and tail functions just give you the top 6 entries, or basically your entries from that particular data set. Now the question is, how do we work on this data? So I can get a statistical summary. So I have the iris data set which we had here. So if I do a head, it shows me iris data set. This is a popular data set which shows the petal length, sepal length of particular flowers and the species, what is the length, what is the width, and what species does that flower belongs to. Okay, now here we can get a summary, that is statistical summary of a data set, which gives me mean, first quartile, median, mean, third quartile, and maximum values. It basically shows you the count of the entries for each species what we have under the species column. Now what I can do is I can check the structure of this data set using str. I can create a data frame now of this data using the data.frame function. So for that we need to also have, say for example, if we would want to create a data frame, let's see how do we do that. So first we create a vector of days, we can create a vector of temperatures and rain, and then we want to create a data frame out of this. So I use the data.frame option. I pass in my days, temp, and rain as the vectors. And now, if you look at the data frame, you basically see that I have my days, my temp, and rain. So those were the variables, those were the vector names, and those have become the column names. Row names are auto assigned, and basically we are seeing the values which have been passed in my data frame. Now I can do a summary on this to basically look at what is the length or how many values we have in data frame, what is the class of elements, so that is character. You are looking at your values or summary, which gives you mean, first quartile, median, mean, and so on. And then it also shows you the complete data on rain. What is the mode here? How many false or how many true values we have. You can also look at the structure of this data frame by doing a str, which gives me how many objects we have, how many variables we have, what are the different variables, so that is days, temperature, and rain, and the values for those. For days, if you notice, it is of the type character, temperature is numeric, rain is logical. Now, how do we do data frame indexing? So like your matrix, which basically has rows and columns and in multi dimensions, similarly in data frames also you have indexing. So you can do a data frame. So I could just extract the first row by doing this, and that basically gives me the value. So you can always compare it by just typing a df. So that's my data frame. And now let's look at the values. Extract the first row, and that shows me Monday 25.6, rain value is true. Now I can also do it column wise. So for example, I could do it in this way. So here what I'm doing is I'm doing extracting the second row from this one. So it tells me 25.6, 30.1, 40.0, 37.3. So you have extracted the values for the column, right? So I would not say extract the second row, you would say extract the second column. Okay, so this one should be second column. Yeah. Now selecting using column names, so that's the easiest way to extract the values for a particular column. So I can just do this. Instead of giving the position of the column or the column number, I'll give the column name, and that gives me all the values of temperature. And if I do this where I'm saying 2:4 and then I'm giving the columns, so it gets me the second, third, and fourth rows for day and temperature. And we are looking at the values. So you have given your row names and then you have selected your columns. You can also do a $sign if you would want all the values of a particular column. So I can just do a df $days or df $rain, and it shows me the values from my data frame. Now, one more way of doing that is using your bracket notation to return a data frame format of same information. So if you want the resultant data in a data frame format, you can just do a df rain or df temperature, and that is basically giving a data frame. So if I had assigned this to a value, and if I had looked at the type of this, that would be data frame. Now, one of the things which we also require is filtering data frames using a subset function. So that is subsetting the information from a data frame. So we know we have our data frame. Let's look at our data frame again. So that just reminds of what data values we have. And here, let's get a subset out of it using the subset function. So I'm passing in my data frame. I am saying I would be interested in the rain column. So I'm giving subset rain column, and wherever the values are true. So returns all the columns where it has rained. Similarly, I can do a subsetting by giving a value for temperature wherever the value is greater than 25, and that shows me the value. So this is where you're filtering the data in data frames using a subset function to which you have to provide a column name and then giving a condition. Now, one more important thing which might be required is sorting your data frame using order function. So I can create a variable by name sorted.temp. I want to do a ordering of data frame, and here I'm doing a ordering based on temp. And now if I look at the value, or I can create this in an ascending order. So let's look at the values. And now if I look at my data frame, it just gives me the order or the ranking for the particular values. So we have discussed this in other section also. So what I can do is I can return all the columns with temperature sorted in a descending order. So right now what we were seeing was we were seeing in an ascending order, but what we can do is we can do that in a descending order. So here I'm creating a variable descending.temp. I'm doing a ordering, but when I'm doing a ordering, I'm using the minus symbol. And this one, if you would look at in the form of a data frame, it shows me the values which are ordered in a descending order based on the temperature column. Now, another way of sorting is by using a particular column. So what I can do is I can sort, I can do a order, and then I can choose the column based on which I would want to order it. And then if you would want to get the values of this, so it tells me the values have been ordered based on temp. So this can be very useful when you would want to sort the data or order it in a particular way to basically understand your data or to make more meaning out of it, right? Similarly, one more requirement might be merging your data frames. So here I'm creating a data frame. So I'm saying authors and I'm using data.frame function. And what we are doing is instead of creating 3 vectors, I am basically doing that within my data frame function. So let's do that. And now what we can do is at this point of time, I can check what my authors look like. So this is my authors. Now here, if you see, we have the vector Turkey, Venables, Tierney, Ripley, and McNeil. So that becomes my first column, which is surname. Then you have your nationality, and then you have deceased, where you have also repeated the values 4 times, right? So that's something new which you might be seeing. So you are creating a vector where you are passing in a value, and for other set of values, you are basically using a repetitive function. Now, similarly, we can create a data frame called books, and this one is where I am having name column, title, and then I have other dot author, and you are passing in the values. So at this point of time, if you would want to look at your books, it would look something like this. So you have given a name. Now just closely look at the data frame function. So here you are using the names, you have the titles, whatever values you are passed in. Always remember, when you have multiple vectors, they are ending with a comma, right? So do not forget that. And then you have other dot author. So that's the name of the column. And you are passing in the values, where you have also passed some NA values. And at this point of time, you can look at authors. This is your books. And our intention will be to merge these data frames. So that's what we would want to do. Might be we are interested in getting the data together. So what I'm doing here is I'm saying M1. Now I want to use the merge function. I pass in my data frames, that is authors and books. So if we closely look at authors, it has 3 columns and 5 rows. And here you have 3 columns and we have 7 rows. So we would want to do a merge. So we'll say authors books, and we will say by dot x. So this is where I'm choosing which is the column based on which I would want to merge. So I have by dot x, which is surname, and by dot y, which is name. So we would want to merge the data where we are giving a condition based on values in surname and name. So you see there is Turkey here, there is Turkey here, we have Venables, we have Tierney, we have this one, we have Ripley, which we have here, multiple entries, and then you have McNeil. Now we don't have R core, which is there in your author. So let's see what happens when we do a merging here. Okay, and now we see the result of this merge, where it has taken all the values from both the data frames. So you have surname, nationality, deceased, you get the title, you get the other dot author, which you are getting in from your books, and the name column is avoided, right? Because we are doing the merging based on surname, and but y dot name is name, so we don't see the name column. But what we are seeing here is the values which have been merged, and then you can compare. So for example, let's do a random check. So if I look at McNeil, that's the surname, or here it was name. So you have McNeil, you have a nationality which comes from the first data frame, deceased from the first data frame. Then you have your interactive data analysis, and then you look at title.author. What you don't look at in the merge is this R core, because this does not have any value in your author's data frame. So you can do a merging of your data frames using the merge function. So please try it out, and you can create different data frames and try to use this. Similarly, you can manipulate a data frame. So for example, here we are creating one more data frame called sales report, which is data.frame. You are giving an ID, product has some values, unit price is where you are getting the values as integer and quantity as integer. So now if I look at my sales report, this is the values which I have. Let's spend a couple of seconds to look at this value. So ID value is 101 to 1010. Product is A, B, so that is automatically assigned. Unit price is starting where you say 101, 140, 184, right? So we are using a as.integer, we are converting it into integer, and basically we are assigning these values here for your unit price. And similarly for quantity, we are assigning the values by doing a as.integer and then just doing a run if. Now, once we have done that, we have created a data frame. Now, how do you transpose? What do you mean by transpose? So transpose is when you are changing your accesses. So if I do a transpose on sales report, and if I want to do a view, so you will see the positions which have changed. So you have all these values. So my row names or row whatever values become the column headings, and basically your column headings becomes your row names. So that is what you're achieving by doing a transpose. You can do a head to look at some initial values. You can do a sorting of this data frame by using the order function, and you can choose the column and also the order if you would want to have it in ascending or descending, or basically increasing or decreasing values. You can also choose a particular column, like we are choosing product as a column, and I would want to take the values of sales report in a descending order, that is unit price, and we can just do ordering of data frames or sorting the values in data frame. So this is pretty easy. Please spend some time in practicing these things, taking these examples, and you will learn more about these functions. You can always try creating an example at your end, and you can try to look into these. Now, what about subsetting the data frame? So when you're saying subsetting the data frame, let's do a subset function like what we used earlier. I will say subset.product A. I'm using the subset function, and here I will get the subset based on the product value being A. Let's look at this, and this shows me only the values where product value matches A. Now extract the rows for which product is A, and unit price is 150. So you are still doing a subsetting, you are still passing your data frame. Here you will give the product is A, which will tell basically the values for product, and unit price greater than 50. So you're giving some conditions and look at the values. Now, if you're only interested in particular columns, so if I say only the first and the fourth column, product is A and unit price is 150. So you have to still use your subset function, pass in your data frame, product will be given as A, and unit price should be greater than 150. But what I'm interested in is the values from the first and the fourth column. And now if you see, it shows me the values for my fourth column. What we can also do is we can create two subsets. So set A from data frame, where we take the product as being A, other one is being B, and then we can look at the values. So this is just A, this is just B, and what we can do is we can combine them or we can merge them using column bind. So when I say column bind and I'm saying set A, set B, so it is basically going to stack the data frames column wise, and if you do R bind, it is going to stack the data frames row wise. So we can either use column or we can do a row wise. So this is in one way where you can merge. The previous example where we saw merging was based on a particular condition which is met based on some columns which might have similar values, right? And this is where you are straight away merging the data frame using column bind and C bind. So if you compare this with the other merge operation, what we saw here, this was where you are comparing the values of first data frame and second data frame and then merging. But here we have just used column bind and row bind, so we are not merging on a particular condition, we are just stacking them either column wise or row wise. Now what we can also look at is doing some aggregate operations. This is going deeper into data frames. So when you use an aggregate function, you are passing in your data frame, you are choosing the quantity column, and then you are basically using the list function. So list function is going to work on your data frame on the product column. So product column for your sales report. So at this point of time, let's look at sales report and let's look at the value here. So this is my sales report, and what we want to do is we want to aggregate the values on quantity column. But for that, I will say I will just take the product columns and I will get a sum wherein I'm ignoring the NA values. Let's look at this, and that gives me an aggregation value. So remember, aggregate function is doing a summing up. Now here we are doing a summing up on your product, that is sales report product column is what we have. So you are kind of grouping by based on product. So we have two products here, A and B. Now what we also want to do is we want to take the quantity column. So that's why we have given that first. And what we are doing is we are doing a summing up. So we are summing up all the values for A and all the values for B. And we are seeing that here, if there are any NA values, we are ignoring it. So these are some basic operations on data frames or matrices, subsetting them, extracting useful information, using some inbuilt functions to do transformation or computation and extracting some values. Now similarly, we can also work on lists. Now that we have looked at data frames, matrices, vectors, let's also look at one more structure and how we work in R when we have to work on lists. So list is basically a structure here, and what we are doing is we are creating a list by using the list function, and here I am passing in three vectors you see here. Now C function is being used. Now in vector we know that all the elements are of the same type. Now let's create a list wherein we see three vectors which are of three different types or objects of three different types. So let's create this list, and now let's look at our list. So it basically has elements wherein you have values of different types. We can create a different list which can also have sequence elements, that is 1 to 10, a matrix which is of 3 dimensions, and then also passing a list. So this is also one way of creating a list. Let's look at list 2, and if we look at the values here, list 2 basically has a vector which has values 1 to 10. It has a matrix of 3 into 3. It has a list which has values A having 10 and B having 20. So this is how you can create a list which can have objects of different types. So we can also use recursive variable, a variable that can store value of its own type. So for that, you have to use a recursive function, something like this. So I'm saying is recursive and then do it on your list, and we can check if the list basically has a variable that can store values of its own type. Now, one of the main requirements when you're working with lists is indexing. So I have created a list, and here I can access these elements by using an index. So if I do this, this shows me the matrix. What I could have also done is using the dollar symbol and then choosing particular element of the list by doing a mat, which is the name given to our matrix, or by choosing a name that is vector. So you can access the elements using indexing or dollar notation or giving the name of a particular element. Now I can also work on list and I can get the third element's second value. So we can do that, and that shows me 20, or you could have done by giving the value 3, that is the third element, and within that you are looking for second element. So I can get the length of the list, I can get the class of the list, which shows me it is type list. And what I can also do is I can convert vectors into list. So here we are creating a variable price, which is being assigned a vector which has 10, 20, and 30. And now what I want to do is I would want to convert this vector into list. And for that, I'm using the list function. So I am creating a variable called price list. And then I'm saying as dot list. So that's going to convert my vector into list. And now let's look at price list, which shows me a list, or you can look at price, which is a vector. So that's when you're converting your vector into list. Now, how do you convert your list into vector? And that also can be done by doing a unlist function. So I can basically work on price list wherein we converted vector to list, and I can just do a unlist on that, which will convert my list into a vector, looking at the values of the vector. Now, sometimes we may want to get the dimensions. So we can use the dimension function to convert the vectors to a matrix so that it can have multiple dimensions. So here we create a vector which has 4 values, and then I'm going to give a dimension to this so that it is converted from vector into matrix by giving dimensions 2, 2. And now if you look at price 1, it has basically changed into rows and columns of 2 into 2 dimensions. So these are some simple examples of working with list. Now, when you talk about basic data type functions, we have seen how you use the assignment operator, how you get the data type of a particular variable or the class to which it belongs. I can assign different values such as 10.5. So the previous one was showing me the value numeric, and now what we would want to do is we want to assign a value 10.5. Look at the class of it. It says numeric. Type of it shows double. So by default, it belongs to the double class. Now I can check if the values in N1 are numeric, and that shows me true. And similarly for N2, and that shows me 2. So you're using the numeric function, which returns true if the given value is numeric. Similarly, we can have integer assigned to a particular variable, and for that either I can do as dot integer or I can assign a value with capital L. So I can do this and look at the value of I1, similarly I2, and look at the values. And if I would want to check if that is an integer, let's look at the values of I2, which was an integer, I1, which was an integer, and I3, which is an integer. So here we have assigned integer values to a particular variable. Now all integers are numeric, but all numerics are not integers. So let's check that. So if I do a is numeric on I1, which was assigned as dot integer 10, that shows me true. If I say is dot integer on I1, so was that an integer? And if I look at the value, it shows me true. Now let's look at the character values. So if we say C1, C2, and look at the class of this, it shows me it is of character type. Similarly on C2, and you can always validate that by using the character function. You can also use some inbuilt functions such as converting to an uppercase or getting a substring from the starting till the position what you would want the elements. I can do a paste function which basically will give me the data combined, or you can say concatenated. You can also use a paste 0 which we know will get rid of the space and it just concatenates them without a space. I can also use a specific separator which we have seen examples, and we can do that. And what we can also do is we can replace set of characters. So here I am saying substitute, and then if I look at the values, it has basically replaced Rob with Senna. And let's look at the length of it or number of characters in this. So these are some basic operations what you're doing on matrices, on your data frames, on your lists, and also on your variables, where either you are assigning them values of a particular type or you are changing the data types. You can also go for coercion. In case of vectors, we have seen that, where if you are passing in values of different types, that's coerced into same types. So later we can learn more on functions and flow control and how that is handled in R. Let's learn how R can be used to take care of flow control. That is, if I would want to have a if else condition, and if what I would want to compute, or if I would want to check some values, how R can be used. So here, if statement consists of a Boolean expression which is followed by one or more statements. So we can just say if, we can pass in a Boolean expression where we would want to compare particular value or we would want to check a particular value, and then whatever is passed in the statement will get executed. So what we can do is here we can use assignment operator. I can pass a value to X. Now we can always do a type of, and that can tell me that X is basically an integer. And now I can use my if, where I can say is dot, and then I can choose integer, and I would want to check the value of X. If that is an integer, then I will just use brackets and I'll pass a statement here. So let me say print, and let's say X is an integer, and we can execute this, and this tells me that the Boolean value is true. Now if, for example, we would have done something else, or say for example, instead of integer, if I had used let's say character for that matter, and we can check the value and we can do this. So here we will check the values, and it says there is an error with the bracket, and let's check this one. So if X, because we missed a bracket here, so let's do that one and then try this, and it doesn't show me any result. So how could we handle something like this if the Boolean expression does not match to true? And in that case, we can always go for else statement. So we can check for a value. So if the Boolean expression is true, statement will be executed, and if it is false, then next statement will be executed. So we could have done the same thing here, where I said print X is an integer, which we know is not true. And what I could do is I can here, after this one, say else, and then I can open up one more bracket, and then I can say print, and I will say X is not a character. And now we know that X is not a character. So this is a simple way where you can use if else, and you can control the flow by passing in the conditions. Now that's when you're using if else statements. Now what about while loop? So that also can be useful when you're programming in R. So an else statement is executed when the condition in the if statement results to false. So that basically means what we can do here is let's pass in a word or a set of words like this. For example, let's say v, and then we use C function to create a vector, for example, and then I can just say hello world. And if you look at v, you can look at the class of v, it's of characters, and if you look at type of v, it is having the objects or elements as character. Now what we can do is we can basically then say count, and let's assign this a value 2. Now what we would want to check is the count of elements in our v equals to 2. So what I can do is while my count is less than say 5, now I'm saying I would want to do something while the count is less than 5. So we have already given a value to count as 2, and now what I can do is here I can open up a bracket, I can say print, and then pass the value of v, and then what we do is not only this, we will also increment the value of count, and we will say count plus 1, and here it gives me error, probably because we have missed a bracket. So let's see what we are missing out here. So let's just check this one again. So here it is. We have created v, which has 2 elements of the type character, and then what we do is we assign count a value of 2, and we would want to check while the count value is less than 5, we would want to print the value of v. So what we are doing here is we are saying while, then you pass in an expression which will check the value of count, we do a print, and then we increment the value of count. Now this is a simple example where you are using while to basically test an expression, and while that expression is true, you would be doing something whatever is passed within your brackets. Now we could also be going for loop. Now for loop is basically used to iterate over a list of elements or a range of numbers. So for example, if I have a vector like fruit which has some values, I could just say for I in fruit I would want to print something. So let's try this also as an example to test our for loop. Now we can just say names, and we can basically then assign values to this. So let's say VJ, AJ, DJ, and let's say SJ, and let's create this. Let's look at the value of names. Now what I can do is I can use a for loop, and I can say for I in my names. So I will say for I in names. Now what do you want to do? So open up your brackets here, and then we would want to say print I, and then basically close the bracket. So you see, for every element in this vector, it is basically going to print the name one by one. So you're iterating through a set of objects by using a for loop. Now this is how we can work on for loop. So if else, while, and for loop can be very useful when you would want to iterate, or when you would want to check the value of an expression, or when you would want to loop and do a particular task. It's always good to understand how you manage flow control in R. That is either when you're working with your for loops, your while loops, also understanding how you can use your logical operators for working with your data in R. So let's look at some examples and understand logical operations. So either you could be having and, or you could be doing a or where you're evaluating one condition, or you're using not. So these are your logical operations. Now here I can assign a value to x, and then I can check if my x value is less than 10, and it shows me false. So I have been checking the value of x. So let's see, is it greater than 10? And that's true. Now I can use logical operations here. So I can say and so I'm saying, is my x value less than 20? And is my x value greater than 10? Now both these conditions are not true. So in this case, we get the result as false. But if I say x is greater than 20, which is true, and I am saying x is greater than 5, that's also true, and x is equal to 25. Now, whenever we are talking about and, we have to look at all the conditions have to be right. So let's look at this and we get the value as true. But if I say x is greater than 10 or x is later than 5, then one of the condition has to be true, which is true in our case. So we get the result as true. We can take a different example. We can say, is x less than 20, which is not true, but is x equals to 30, and that's also not true. So in this case, we get the result as false. Now we can straight away compare some numbers and we can say, is 12 equals 3, and that's false. And if I say not, then that basically will give me the result as true. So these are some simple logical operations which help you when you're working with your data in R. Now we can create a data frame by using an inbuilt data set, empty cars. And let's look at our data frame. So that shows us the values with all the different car models and the different column names. So car models are the row names, and then you have other things like mileage and cylinder and so on, which are the specification for the data. Now what I can do is I can filter out values here using indexing. So I can say data frame. Now in that data frame, I would want to compare the value of mileage, which is greater than or equal to 30, and then I can end it with comma. So that gives me the value wherever the mileage is greater than 30. I can also do a subset on data frame where I can select a particular value. So we can be doing this, or we can be using square brackets. We can also do a dollar and compare the values. Now we will use our logical operations knowledge here. So we will work on data frame where I'm interested in the mileage, which is greater than 20, and I'm looking at the column HP, horsepower, and that should be greater than 100. Remember, when we are doing a and, both the conditions have to be met as true. And that shows me the result where you're looking at the mileage and you're looking at the horsepower column. Both of these are met, and that's why we get the result. So these are some simple examples of using your logical operations, either when you're working on a data frame. So same thing can be done on a matrix, same thing can be done on a list or a vector or individual values. Now let's also learn about flow control, that is how if else or else if is handled in R. So you can do a single condition check. So for example, I assign a value to hot, which is false, and I'm saying temperature is 50. Now what I would want to check is if the temperature value is greater than 60, which in our case will not be true. Which will not be true because temperature has been assigned 50. So is it greater than 60? No. So if I do this if condition, and I'm saying if the condition is true, then I would want to assign the value of hot to true. And now if you look at the value of hot, it is still false. Why? Because the condition which we passed for our if is not true. It has not been met. So whatever was passed within the statement has not been done. Now let's change the value of temperature as 100. And now if we do the same thing, we say, is my temperature greater than 60, which is right. So then whatever has passed in the bracket will be applied. So hot will be assigned new value. And now if you see, the hot value is set to true. So this is a simple single condition check what you're doing. Now certain times there can be multiple conditions to check, and that's where we use else. So in this case, we go for assigning a value to score, which is 63. So let's do that. And now let's say, is my score value greater than 80, which is not true. So whatever is passed in here, which is print, it's a good score, will not be done, but it will jump to else, and then whatever we have passed in else will be done. So it will say it's not a good score. So let's do this if, and it says it's not a good score. So this is a simple way of using if else, where you are checking two conditions, or you are checking the condition, but what if the condition is not met? Then your control is passed to your next statement. Now I can also do a else if. So I can say score is 63, and I can say is my score greater than 80? That's my first condition, so it would print good score. But might be I would want to check something else, so I'll say else if, and I'll say is my score greater than 60? Yeah. And is it less than 80? Remember the and, which has to evaluate and true for both the conditions. So I'll say print decent score. I can still keep on giving conditions here in else if is score less than 60 and score is greater than 33. That would not meet, so that will be ignored. And then you have else, which says print poor. So first it checks or evaluates for the condition which you have passed for if. If that doesn't work, then it goes to else if, and if anything in else if is met, then it's going to take that into consideration and it will not go for else. If and else if conditions are not met, then it goes to else, and we see decent score already printed here. Now that's a simple example of if, else, and if else if, wherein we are evaluating a condition, but probably we have multiple other things to check. Now, how do you work with while loops in R? That's very simple. So what we can do is we can assign a value to x, and now I will say while my x is less than 10. So I'm going to create a loop. So I have said my x has been assigned a value of 0, and that's fine. So this is going to be less than 10. But if we are going to just do this, then it will keep running and it will get into an infinite loop. So we'll see how we do that. So we'll say while x is less than 10, I would want to basically have the value of x. I would want to print x is still less than 10, adding 1 to x. And what we are doing is we are incrementing the value of x. Now, if you do not do this step, then it will get into an infinite loop because x will be always less than 10. So we are incrementing the value of x by 1, and then we are giving a condition. So if at any point of time x is equals to 10, I would want to say x is equal to 10, terminating the loop, and then basically my while loop ends. So we can do this. So let's say x is 0 and then do this while loop, and now you see it is at every step it is basically printing out the value of x. It is still less than 10, adding 1 to x, and it also gives you the value of x. So when we do a x is currently, and I print out the value of x, so it shows me 0. Next time you increment it, it becomes 1 and 2 and so on. So this is where you are using a while loop, where you are looping where based on a particular condition, and then you basically have, once the condition is met, you are able to complete the loop. Now let's look at, let me take this one here. We'll look into functions in a later stage. So let me take this function and let's get rid of this one. I would also want to talk on break statements and while loop. And once we are done with the flow control on while loops, then we can look at the functions aspect. Either we can look at how we control our functions or how we create built-in functions. So let's look at this one and let's continue with our while loop. So we just saw a simple while loop here. And what we also want to see is when you're working with your while loop, how do you break if a particular condition is met? So we saw a simple example of while loop, and that's fine, wherein we were printing out something, we were auto incrementing the value of x. We were also checking at one point of time within our while loop, if the value of x was met, we would say we are terminating the loop and it comes out of that. Now, if that does not happen, then we continue doing it. How about a break statement? So break statement is when you would want to end the while loop, if a particular condition is met. So for example, here I assign a value to x, which is 0. Now I want to evaluate this lesser than 5. So that means I will be auto incrementing the value of x. So I'll create my while loop. I'll give in a condition that x is less than 5. Now what I want to do is I want to use the cat function, which will print the value. So I'm saying x is currently, and I am printing out the value of x. Then I say print x is less than 5 because we have not yet incremented the value of x. We are adding 1 to x like what we saw in previous example. I am saying x is then incremented by 1. And here I'm saying if x reaches 5. So while we keep incrementing the values within the while loop, we'll see if x's value is 5, we will print it is equal to 5, and we can just do a break. Now, if you do not use a break, you can still end the while loop, but break is basically to end this loop here based on condition which is met, and we can do this and then run this while loop. So you see here x was met as 5 and we just broke out of the loop. So that's your simple while loops, what we are seeing. Similarly, we can work on for loops. So for loops can also be useful. So your conditionals, what we saw as if else or else if, your while loop is while a condition is not yet met, you keep looping and keep doing some actions. Now what you can do is you can also work on for loops. So here I'm creating a vector and then I am going to loop, that is I'm going to iterate through every element. So I'll say for, and when you're using for loops, you'll say for, and then you can give in anything. You can give in any value. I can say I can say x. So I'm just giving temporary variable in vector and then I'm printing it out. So this basically prints all the values one by one. So there is one more way to do it. You can say for and you can say I in, and I would want to take length of the vector. So 1 to the length of vector, that is till the last element is reached. I would want to print the vector elements using the value of I. So what is I here? It's the index position, and I can do it in this way. So if you are looping over a list, so I'm creating a list and it's very simple. So you can just do a for loop where you can say for I in list, I want to print the I, and that gives me the list elements. Or you say for I in and you give from starting position, that is 1, till the length of list, and you would want to print every element. So here we can also use double brackets. So if you would want to loop through a matrix, so sometimes that might be required. So let's create a matrix which has 1 to 25 values around by row, and you look at your matrix, and now what you want to do is you want to iterate through a matrix. So you want to do a looping. So I'll say for I in matrix, I would want to print out the values, and that prints out all the values in matrix. Now what if I want to print the square and square roots of numbers between 1 to 25? So I can say for I, wherein the value starts with 1, ends with 25, and then within my for loop, I can basically give this condition where I'm saying, get me the square root, that is I into I, or get me a square root of I, and just print it out. So I'm saying message I is this one, square root is this, and my square is this, and square root is this. So if I look at this values here, now I am looking at all the values from 1 is to 25. I'm looking at the square of the values, and I'm looking at the square root. So what we did was we did a for. We passed in the elements by saying I in 1 to 25, and within the bracket I have said what do I want to do for every element. So either I've calculated a square, I've calculated a square root, and then I'm printing out when I'm using the message function, which takes the value which you are passing in, comma, the value of I, similarly square, and similarly square root. So these are some simple examples of understanding flow control in R. That is, using your for loops, your while loops, and also your if else. Later, we will spend time in learning about functions, which could be either created by the user or built-in functions, and also factors in R. Welcome to this section of R programming, where we will learn about functions, whether that is about inbuilt function or creating your own functions and working on your different data structures. So what are functions? Function is basically a set of statements to perform a specific task. Now, R has a large number of inbuilt functions, or you can say packages, which you can import and start using, or users can create their own functions. So when it comes to functions, the syntax is very simple. You give a function name, you can assign your function to a variable, and a function can take no arguments, one argument, or any number of arguments. So let's see some example on functions. So for example, here we are creating a variable called squares and we are assigning a function to it. Now this function would take one argument, which is a, and then we use a for loop. So we say for I in from 1 to the number a, we would basically be doing a exponential computation. So what we would do is we would square the value in this particular range and assign that to b and print it. Now when we do this, we can call in this function and pass in a value to look at the square of that particular value. Now this is a simple example of function. So this is how it would look depending on what value you have passed to the function. So for example, we say squares and we pass in a value of 4. So that becomes for I in 1 to 4. So you would start with 1. The value of 1 square would be 1. And then you have your value for 2. So 2 square would be 4. Then we have 3. 3 square would be 9. And then we have 4 square, which is 16. This is a simple example of function. And this is how you can create your own function to calculate or carry out some computations. Now let's look at some other examples before we get into built-in functions, which basically allows you to work with different data structures. So there are different mathematical functions which can be used for your data science or computations. You have your regular expressions which can be used for pattern matching, or you can also use functions for data manipulation. Now, before we get into data manipulation, let's look at how you work with functions, taking some examples. So let me bring up my RStudio, wherein we will try out some examples and see how functions work. Now, here are some examples and we can see how this works. Let me just clean up the console and we can start here. Now here we are creating a simple function which does not take any argument. We call it as hello world, and this will start with the word function and parenthesis. Now that could have arguments passed in. However, this function, we are not passing in any argument. And what we are doing here is we are printing out whatever value is passed within the bracket. So let me just do a control enter. My function is created, and you can straight away call this by just doing this. Now, however, if you would have tried this function without the bracket, for example, something like this, then it would have printed out the complete function. It would have printed out the complete function and whatever you passed in to hello world. But if you would want to call the function, then basically you would just do hello world and then use the brackets. So that's how you call the function, and that's how it shows the result. Now, your function can be with a single argument. So for example, here we are passing in an argument called name, and we can then use this to pass a value to this. So here I'm saying hello name. I have my function, but this one takes a single argument, and we are going to use paste, which basically can concatenate or just adds up whatever you are passing in to paste. So we will say paste hello and then the name. Notice that I have given a space here after hello so that I can have it in the right format, and I can just do this. So the function is created, and now let's pass a name here and just try to call the function. So name is one argument or a single argument which is passed to this function. So let's look at the result, and that shows me the name whichever was passed to this one. Now what we can also have is function created which takes two arguments, and this is a simple example. So here we are creating a function addNum. I'm saying function, it takes two argument. I'm not providing any value or default values for this. We'll see some other examples for those. Now here this particular function takes two arguments, and whatever you pass in here, a addition of that will be seen. So let's create this function and let's call it and test it, and that shows me the result as 70. Now what we can also do is we can add a vector to a number. So vector is list of elements or list of objects, you can say, and here we would want to perform addNum, or we would have to call addNum function by passing in vector, which becomes the first argument, and the second value is the next argument. So let's run this one, and that shows me the result wherein 5 as a value has been added to every element of this particular vector. Now when it comes to function, you can also have default argument values which can be passed. So here let's look at as an example. So we have hello name again, but this time instead of passing in just an argument, we will also provide it a value, or you could say that could be considered as a default value. Now when we create this function, we are doing the same thing as previous examples, but we are passing in an argument, and that argument has a value. Now once I do this, I can surely call this function without passing in a value, and that shows me the name which we had assigned to the argument, or we can even pass in a new name which will be assigned to name. So if we do this, it works in both the ways fine. So this is in one way you are passing in a default value, and then basically you can either call the argument or you can assign it a new value. So if we would do something like this, hello name, and then for example I would say name equals say Jerry, and if I would do this, so that also works fine. However, since we are passing in an argument, we are assigning a value, so either we can let it go for the default, or we can just pass in the value, or we can be very specific in mentioning the argument and then the value for it. Now how do we return value from a function? Let's look at this. So here we are creating a function, we are calling it full name, and this one takes name wherein we are giving Sachin, and title is say Tendulkar, and what we would do is we would use a return statement here. So return would basically use the paste function. It will take the values of name and title and then glue them together. However, we are using also a space so that there is a space between these two values to the arguments which are passed. Now if I run this this function, my function is created. Now we have already passed named arguments, or we have already passed value to those. So we can straight away say just call the function, and that does whatever you have mentioned in the function body. I could have also said that I could create a new one wherein I will pass new set of values which we saw in a previous example, and then if we call this, it takes up the new values. So either you can let it go for default like what we did here, we can also pass in new values, or if you would want to keep it specific, you could basically say full underscore name, that's my function. I could say name equals, and I can say John, and then I will say title Smith, and that's also fine. So we can do this, and that works in the same way as it would have worked with just passing in the names. So this is fine. And if you would want to test it out, say for example, if I would just take off name here and just do this, that also works perfectly fine, wherein we are still using these arguments in the particular order. Now, if I would have changed this one to name, wherein I am already passing in a value for name, and if I tried this, so in this case, what happens is name is Smith, and basically your title becomes John, right? So we have to remember how we are, what arguments we are passing, and if we are basically assigning values to the arguments or letting it pick up the default ones. So let's do this, and that looks okay. Now, when you talk about scope of a variable, okay, now before we understand scope of a variable, let me show you some more examples on function. Now, say for example, if you were using built-in functions, we have lots and lots of built-in functions which are available for programmers, which they can use in their data science activities or data processing or computation. Now here we are using a function called rnorm to generate 1000 random values from a normal distribution of mean 0 and 1. So I would use the rnorm, that's an inbuilt function, and I will call this, say, normal distribution. So that is already done. Now we can find out the mean on these random values which would have been generated using the inbuilt mean function, and that works perfectly fine. You can also create a histogram out of this, and if I do this, it shows me the histogram. So let's see the histogram here. Let's bring it out, and that shows me the histogram of normal distribution. If you would be interested in knowing about a particular inbuilt function, you can just do a question mark and use the function, and that basically shows you the documentation of the function. So this is a generic function which computes a histogram of a given data value, and here it takes arguments. So this is basically your data. This could be the number of arguments which you are passing in for your histogram to be created. Now we can look at some more examples here. So I can say to histogram with large number of interval breaks, and this is where I'm also specifying breaks and passing in a value. So this allows me to provide arguments to functions by position. Now the same example which we have given here, we can do it without breaks argument, but as a good practice, we should actually give name to the arguments which we are defining. So if I would do this, wherein I'm passing in my data, that is normal distribution, and then for breaks, I'm just giving the value 50, and that is also fine. It works perfectly fine here. Now we can create our own function, which, as we saw in some basic examples, functions which can be without arguments. Say this is a simple example, or with arguments. So this one we have already seen how you can create a function without giving any argument, or by giving an argument and then basically calling in the function. Now when it comes to optional arguments, so we can look at this function wherein I would want to say find out the exponential value of a particular number. So I call it expo value. I use my function. I say this will take the value x. Now that's an argument which we are passing in. We could have given it a value, or we will just let the user provide the value when this function is being called. I will also give a default argument which is power equals 2, and here we would want to get a histogram of the values with a particular power. So if I create this particular function, that's done, and now I will just pass in my value. I don't need to mention power, that has been given a default value. Yeah, if we would want to change it, then we can pass in that. So let's run this one, and that gives me exponential value, a histogram based on the normal distribution data, and by default it is using power as 2. Now, what we could have also done is we could have specifically mentioned a different value for power, and that works perfectly fine. I could have just passed in the value as power, and that also works fine. So here you are using named arguments and basically passing in any other arguments. Now what we can also do is we can use these named arguments, and then we can also do, or we can pass these arguments. That is what we call as passing any other arguments. Now if you look at the explanation of this histogram function, if we look at this, it shows me these three dots, and this is what we can use to pass in any other arguments. So let's look at an example for this one. So say for example, I would want to create a function where I am passing named arguments. I am passing in the data, but then I would also want to pass any other arguments which can be passed dynamically. Now for that, we can create a function here wherein I'm calling it expo value again. I'm passing in my x, which will be the data which we'll pass in. You are mentioning power, which is 2, which is a named argument, which can also be considered as a default, or you can change the value, or you can provide a new value. And then I'm also giving these three dots, which are also passed in within this particular function. So let me create this function here. Now once that is done, then I can call this function by passing in my data, which is normal distribution, power is 2, and then I'm also using these breaks for getting my histogram with intervals of 50. So let's call this function, and that gives me the histogram. Now what we can also do is sometimes it might be useful to pass logical arguments. So for logical arguments, what we can do is we can create a function which will take the data. Here I'm using a named argument exp, that is for exponential. I'm saying if the value of histogram is false, and then I'm also giving any other arguments. So what we will do here is in this function, we will say if the value of hist is true, then this block of code will get executed, where you will get a histogram based on the exponential which has been assigned in the function passed as an argument. And if that doesn't hold true, which is by default false as we have given in our function, then this piece of code will get executed. So let's create this function, and that's done. And now we can straight away just pass in our data. Exponential value is given as 2. Histogram has been given in false. That means the else part of the code will get executed. And we can look at the values here. I can also say histogram is true, and that's where we will be calling in the hist function, and I can do this. That shows me the histogram. So in this way, we can pass in named arguments, we can pass logicals, and then we can also pass any other arguments for our use case. Now looking further in functions, let's also understand the scope of a variable in a function. So here I am saying v, and then I'm saying I am global variable. Let's create this. And then I'm saying stuff. So I'm global stuff. So this is basically, we have assigned some values to variables v and stuff. Now let's create a function where I'll say fun. I'll use the function, and I will say this will take my variable stuff. I'm saying print v, and then for stuff, I'm assigning in a new value, and then I'll print stuff. So let me create this function and let's see how it works. So if, for example, I would just say print v, that shows me the global variable which we had created earlier. And since I'm using that within my function, it basically has the value. Now I also have a global stuff. So I'm saying print stuff, and that shows me whatever was assigned to the variable. And now we will basically call the function by giving in the argument as stuff, the variable which we had created. Now, if we do this, then it says reassigning stuff inside the function. And that's because within the function, we are basically assigning a new value to this stuff. Now, I can also just do a print stuff now. If you see, it still goes back and prints the global variable. So only within the function, reassignment happened, and that's what we understand when we talk about global variable or local variable. Now, to create a function to find the final amount to be paid by a customer after adding 20% tax to the purchased amount, how do we do that? So I'm here creating a function which will take x as 100. And what does that function do? We would want to basically find out the amount which is paid by customer after adding 20% of tax. Now, how do we calculate that? So we take x plus 20% of x, and that would be the final amount which will be paid. So we do a return t, and this is my function. So let's create this function, and then let's pass in a value to see what is the amount which customer would pay with an addition of 20% tax. So this is a simple function where we are passing in one argument, we are giving it a value, and then we are doing computation within the function body. What we can also do is we can create a function where I am passing in an argument, and I can then check the value of that. So if the argument passed was greater than 0, then we would find out the final amount, which is amount plus 20% of the amount. If the amount is less than or equal to amount, then equal to 0, then our final amount is equal to amount, and we return f amount. So here we will be evaluating these conditions, and based on that my function will return the value. So let's create this function and pass in a value, and that shows me 100. So you can just test this by saying amount 1, and say for example I would have passed in 0. Now in this case my final amount is 0 because there is no amount which needs to be paid by the customer. Now checking the argument and the body of a function. So we can always use this inbuilt function args, which will tell me for this particular function what are the arguments and what is the body of the argument, which basically tells me whatever we have coded within the function body. Now to understand the scope, we can create a function here which is taking an argument x, and what does this do? So we assign a value to y, then we basically say g1, and here I am using function of x. Now what does that function of x do? So this one will take the value of y plus multiply x by itself. So this is a function which we are creating, and then I am saying g1 of x. So what you're doing is whatever value was passed in as x, for that function x will be applied. So let's create this function and then pass in a value 10, and that gives me the result as 110. Similarly, we can create another function where we want to do some computation, and then I'm creating one more variable which has basically the function, pass in a value for y, and then basically what you do is you are calling in your g2 function, and then let's call in this function. So let's do this, and let's also create f2, and then finally we will call in f2, which is internally calling g2. So these are some simple examples where you are doing some computations and creating some simple functions. Let's also create a function which is taking two arguments. So here I have g2 function takes two arguments, x and y. What does that function do? Here we are saying y plus x into x, that's my g2. And similarly, I'll create f2, which is going to have a value assigned to y, and this one is going to call in my g2 function, which will take x and y, x which we are passing in here, and y which we have assigned. So let's create this, and then let's call our f2. And what does that f2 do? It basically has the value of y assigned, and then it does whatever is mentioned in g2 with our x and y values. So I'm passing in 10 here, so it is basically y, which is 10, plus you have the X value which has been passed here. So let's look at the calculation, which is 10. So that gives me 110. So 10 into 10 into 10 plus the value of Y. So this is how we can create functions which have been assigned some values and then pass in some other values to those. Look at some more examples here when we work with functions and see how we can use functions to carry out our basic operations or calculations. So for example, here I'm creating a function, and this will take an argument wherein we are saying it would be marks. Now let's do this, and the function body would say result is not defined. Now if the marks are greater than 50, then result will be pass, and you will have the message which is your result is, and then you are passing in the value of result. So let's look at this one. So let's create this function, pretty simple function, and then let's pass in a value here. So I'll say status as 60, which will be checked for the value greater than marks or lesser than marks, and that tells me your result is pass. And if we give this one, then it says your result is not defined. However, we can have additional statements here which can say if the result was lesser than 50, then what should have been printed. This is a simple example. Let's look at one more example, and here my argument is age. Now just notice that we are not passing any default values, or we are not passing any values to the arguments. We are just passing in an argument which will be assigned a value when you call the function. Now here we say age group is not defined, we say vote is not defined, and then we start using some condition checks. So I say if the age passed is greater than 18, then the age group would be adult and the person can vote, and message your age group is and voting status is will be printed out. So we can use this, or from our previous learning we can do a if else and modify the function. So let's create this function and then pass in a simple value to this, and that tells me what is your age group and what is your status to vote. So now if we would want to create a function to convert a name into uppercase, let's see how we can do that. So we are creating a function here which takes the value name. Now then we also find out the length of this particular argument, and for that we are using an inbuilt function called n-character, which will be for your name, and you would want to find out the length of this particular name, and we would say if the length is greater than 5, then we are again using an inbuilt function called toUpper, which will convert the argument or the name passed to uppercase. We will say message user given name is, and then you print out your name. So let's call in this function. So let me first create this, and then I can call in this function, and we clearly see that the number of characters in this word is more than 5, and that's why it is converted to uppercase. However, if you would call the function with a name which has less than 5 characters, it says as it is. Now this is again a simple function which we created. Let's see how you can create a function to calculate bonus. Now here we are passing in 2 arguments. So this function takes 2 arguments. One is salary and one is experience. And then we say if the experience is greater than 5, then bonus percentage will be 10, and else bonus percentage will be 5. And here we will calculate the bonus. So first it will find out how many years of experience a particular employee has, and based on that a value of bonus will be assigned, or bonus percentage will be assigned, and then you say what will be the bonus, that is salary into the bonus percentage, and return the bonus amount. So this is a simple function. Let's basically select this and let's create this function, and then let's calculate the function if the salary is 25,000 and experience is 6 years, and that basically will tell me the value. So let's look at the value. It tells me 2,500, which is 10% of the salary. Similarly, if we go for this one, which will basically go for the execution of else part of the code, we can do this, and that gives me bonuses half of it. Now, how do we handle multiple conditions and multiple actions? So let's look at that. So let's create a function which takes one argument, which is age. We would check if the age is greater than 0. Then we would want a nested if within this condition. So if age is greater than 0, then whatever we have given here will get executed. And this will be this part of your code. And here I'm again checking if age is less than 18, then age group would be kids, else if. Now else if is to check the second condition. So if the age was passed, if it is greater than 0, then we get into this block of the code. Now it was greater than 0, but then is it less than 18? Then I would categorize the person as kids. If age is less than 60, then we will say age group adult, else we will say age group senior. Now we can basically say that we could have given more conditions to this, because here we are saying if age group is less than 18, then the individual would be within the age group of kids. If that is not true, that is it's not less than 18, so probably it is 18 or greater than 18, then we are checking the second condition. If the age is less than 60, age group is adult, and if these two conditions are not met, then it jumps to else, where age group is senior. And if this whole block was ignored because age was less than 0, then we would have just printed out age group is not defined, messages wrong age, and your age is such and such. So this is our whole function. So let's go ahead and run this. Now let's check the age group when the age is 10, when the age is 40, when the age is 65, or when the age is minus 10, which is not defined. Now there are some inbuilt functions which can be used in R, such as your switch function. So looking at this function, that is switch function, we can see, or we can use this for our different kind of operations. So here your switch function returns values match with the first argument, and first argument should be a character. Let's have a look at the example. So say for example you want to return the house rent allowance or HRA amount based on cities. So we create a function called HRA. Now that takes an argument which is city name, and here we will say what does this function do. So here I am saying HRA amount, and I'm going to use the switch function. Now switch function, I'm saying I would want to convert the city name to uppercase so that we can maintain some consistency. And here I'm saying if the city is Bangalore, it would be 7,500. If it is Mumbai, 1,000. If it is Delhi, 8,000. Chennai, 7,500. And you have 5,000 value. And you are returning the HRA amount. Now, what do we do with that? So let's create this function. It's done. And now we will pass in the value. So we will see whatever value has been passed to this, and that gives me the value here, right? So switch is basically taking me directly to this value. Now, however, if I try to provide a city name which is not given in the list, so when I'm saying, say for example, Pune, now what is happening is it is just taking a value which has not been assigned to any of these conditions. If I go for again something else which is in a lower case, now this is where your to upper function will come into use. And if we do this, it basically converts this into uppercase Bangalore, and then basically it gives you the value. So this is the usage of a switch function. Let's look at one more example. So for example, here we are creating a salary range, which will take an argument which will be band, and I will say these are my bands, or you can say these are my options. So I can say L1 is basically 10,000 to 15,000, L2 is so and so, and L3 is so and so, and you return the range. Now let's create this function. Sometimes you have to do it this way. So our function is created, and now we can just do a salary range given a value, and that gives me the range of the values. However, if you pass something which is not mentioned, then it basically prints out null. So in R, you can also use repeat, which can be useful. And what does repeat do? So here I am assigning a value to a variable called time. Let's do that. And then I'm giving a piece of code with repeat. Now what does repeat do? So you're passing in a message which is hello, welcome to our tutorial. And then you're saying if time is greater than or equal to 20, you would want to break out from this loop. And then you also increment the times value. And this will keep repeating till this if condition is met, wherein we have said time value starts from 15. So let's do this. And this basically will print out the message wherein first my time was 15, which was less than 20. So you increment it, it becomes 16, you print it again, 17, print it again, 18, print it again, 19 and 20. And as soon as you reach the times value, which is 20, it breaks out of this and it stops printing this particular message. Okay, now let's look at some more examples. So if you say R, we will use, say, a function to find the square of any given user number. Okay, if the square value is less than 100, then increment user value by 1 and find square again, and repeat this till square exceeds 100. Pretty simple. So you create a function which takes n as an argument, and you would want to repeat it. So you would want to repeat this by squaring the numbers until the square exceeds 100. And once it reaches 100, you will break out. So this is what we are doing, and we are auto incrementing or incrementing the value of n by 1 every time we calculate a square, and then you return the value of n. So let's create this function, and now let's calculate it for square 6, and that tells me what is the square. Now as soon as your square value touches 100, it basically breaks out of the loop. Now if you would want to find balance in a bank account after n years, if a person has deposited X amount in the beginning and bank gives a interest of 8% per annum, right? This is a simple calculation. So it needs the amount which was deposited, you need the year, and you need the rate. Now year, which is n years, can be given by the user. Rate, we have already given 8%. However, functions main functionality is that you can even assign new values to it. Say later, 1 month down the line, the bank rate changes, might be it increases, might be it decreases, then function should not be modified. It can just take up the new values and start calculating from there on. Now here we will say get the final balance. Function takes amount, the amount which would be deposited, year, and that could be say 4 years or 5 years or 10 years for which you would want to calculate the rate of interest and add it to the amount. So I'll say for I in 1 to year. So that depends on how many times you would want to run this loop. I would say interest would be using the round function. I'm saying amount into rate, whatever is the rate of interest. And then you are giving 2 years. Now final amount will be calculated. So you are basically saying amount plus interest, and you will pass in a message where we'll say year is the value of I, that's first year or second year. Amount, what is the amount, what is the interest you are calculating based on the round function, and final amount will be amount plus the interest. And then you basically say amount will be given or final amount will be assigned to amount. Now if this is a function, you would want to return the final amount. So let's just select this and then basically create a function. And let's say I would want the final balance. If the amount deposited was 5,000, it was kept in the bank for 5 years and rate of interest was 8. Now that should basically give me my final amount. And if we double that, so we say amount is 10,000, number of years is 10, but the rate of interest is less. So let's calculate this, and that gives me the interest. However, if you notice, based on my message, it is basically telling me what was the first amount, what was the interest, what was the final amount. And it does that for all these number of years. So these are some simple examples for your functions, right? Now we can also look at, on the similar lines, we can create some interesting functions. So you can find the total number of years required to raise $1,000 if the user deposits $750 per month. So here you're not actually calculating the final amount, but you would want to find out how many years are required to basically have the amount as 8,000. So your function, we are saying the amount is say 550 or say 750 per month. Now I would say let the final amount be 0 as of now, month is 0, and I will say while my final amount is less than or equal to 8,000, I would want to do something, and that is you are incrementing the value of month by 1, because that's your first time your amount is less than 8,000, whatever deposit was made, say $750 per month. And then you have final amount, which is your initial amount, which has been assigned to F amount, that is 0, plus the amount. You print out the message, and then you basically say year is whatever value was passed for month. So you may want to have it for number of years or years with particular amount of month. So we will calculate the year value. Now here what we are doing is we are calling in this required years function without an argument, which takes the default argument, or you can pass it with 750. We can run this. So let's create this function. Pretty simple. Done. And if we do not pass an argument, then the amount is 750, and it tells me what would be or how much time it would take for us to reach from say 750 or 550 to final amount. Similarly, if I would have done this, it tells me again a new value. So we are finding out the total number of years required to raise 1,000 or raise the amount to $1,800. So these are some simple examples of functions which you can use for your operations, your calculations, and also creating functions which can be repeatedly used with either one, either no, or either multiple arguments. Now, so far we were learning on creating our own functions, and we also looked at using some inbuilt functions, either creating a plot or basically doing some basic operations or passing in multiple arguments. So let's look at some more examples. And when we talk about built-in functions, there are lots and lots of built-in functions which are available in R, which can be used. So let's look at these. So for example, here are some built-in functions which can allow you to work with different data structures. For example, you have a sequence function which allows you to create sequences. So for example, I could just say test nums, and I can just say sequence, and here I can say where does it start from. So might be I can say 0 goes all the way to 50, and then I can also say if I would want a jump or how many numbers should be used. So for example, let's do this, and now if I look at test nums, so that shows me the value. However, not to confuse, we could have also done this using assignment operator like this, and then look at your test nums. So it tells me It has created a list of numbers from 0 to 50, which are even numbers. Now you can always do a class of, and let's look at this. And that tells me the objects here are numeric. And say, for example, I would use type of to see what is this test nums, which we just created. There was a typing mistake. Let's check this, and it has the values with double, right? So we have created a sequence here where we are creating a list of numbers which have a space of 2, or you are saying about even numbers. Now you can also use a sort function. So I can do a sorting here, and I can give it in an increasing or a decreasing order. So if, for example, I have created this sequence, and I could just create a simple variable like this, pass in a vector into this, which could be, say, for example, I'll try out test nums, and then look at your v. So those are my numbers, and you can straight away do a sort on your test nums. So I could just do a sort on v, and that basically shows me the number. However, I could also do a sort v, and then I could say here, let's check this v comma, and then you can say decreasing equals true, and let's do this. It just reverse or puts the data in a reverse order, or it sorts based on decreasing value and having the greater value in the beginning and the lowest value at the end. So you can use an inbuilt sort function. Similarly, you can use a reverse. Now reverse need not actually sort the values, it will just reverse the elements in your sequence. For example, let's say v2, and I will again use this one as C, and then just pass your test nums. That's an easier way. Or I could have created a new vector. So I'll say test nums. That's my v2, and you can do a reverse on v2, and that basically shows me the values. But here we see, let's see. So we are looking at, okay, so this was wrong. I should have given a capitals and do it. Yeah, this is fine. And we get the values. However, if I had created something like this, v3, and let's say C, and then let's say 99, and 2, and 3, and 4, and 5, and 78, 100. So that's a vector I'm creating. And now what I can do is I can use the reverse on v3, and you see it has just reversed the elements in the list. Now we could have done this without giving these brackets here, and it shows me the result. So this is good to understand what your sorting does. So sorting is basically going to look at the objects, and it's going to sort them in ascending or descending order. Reverse is just going to reverse the elements in your list. Now similarly, you can also use append, which is basically to combine objects. So let's say v4, and that will basically have append, and let's take v2, and let's take v3, and this is what we would want to append. And now look at your value of v4, which basically has everything added into one. So this is your append. Similarly, you have other functions like finding out the absolute value of a number. You would want to find out the square root. You would want to find the sum of all the elements in a vector. You would want to find out the floor value, exponential value of something, and you basically finding out the mean value. So these are some built-in mathematical functions. So you have built-in simple functions, you have mathematical functions, you have regular expressions in R, which can also be used for pattern matching. Now what we can simply do is we can create a variable, let's say text, sorry for caps, let's say text, and here I will pass in something. R is a programming language for data science. Let's do this. And now I would want to use grep function. So I can say grep, and this one needs what I am searching for, So let's say language, and where am I searching for? So I'm searching it in text, and let's do that, and that tells me where is this found. So when I do a grep, I'm trying to find out if this was found in my element. So here I'm saying text and grep language. Similarly, I can also use one more function, which is finding out index positions. So I can also find out index positions by basically giving the vector, and here I can do a grep, pass in my vector a b c d. You are searching for b and in your vector, and that tells you your b is at the index position 2, d is at the index position 4. So here we are using some regular expressions. Now there are also other ways in which R can be used for data manipulation. So let's learn about factors in R, and how do you work with factors and what are they for. So when you talk about factors, so here let's clean this up and let's see what is this. So when you say factors, here we are talking about categorical variables. So categorical variables can take only limited number of different values. Now don't be confused with this histogram example here. Might be we can just look at packages so that that doesn't get confused. So when we talk about categorical variables, we are talking about variables which can belong to only categories. For example, in R, there is a data structure to work with these kind of variables, and that is called your factor. So with factors, we can be sure that all statistical modeling techniques will handle such data correctly. So for example, you can talk about a person's blood group, and you can say the blood group could be A or B or AB or O. So say we collected information about 8 people and we recorded this information as a vector, and we can call it blood group. So let's do that. So let me try that here. So if I say blood group, and then I would like to create a vector here so that we can look at information about 8 people and their blood group, and this can be in the form of a vector which can then be created or converted into factor by using the factor function. So how do we do that? Let's say I have blood group, and here I will basically give in some values. So I will use C function, and here let's give some values. So for example, let's say B, let's say AB, and let's say O, and let's say A again. Let's again say O, might be one more O. Let's say A, and let's say B. So here we have 8 entries, and let's consider we have recorded the blood group of 8 people, and this is in the form of a vector. So for example, let me create this. Now this is a vector which we have created, and you can always look at the value of this one. So let's say blood group, and that basically, okay, there was a spelling mistake. Let's do blood group, and that basically shows me the values. And here you see all the values that are in double quotes. Now we have basically created a vector. Now to convert this vector into factor, we can use the factor function. And how we can do that is basically we can say, for example, let's go here and let's say blood group underscore factor. And to convert this vector into factor, I will use the factor function and then basically pass my blood group here. And now I have created a factor, and we can look at this factor by just doing an blood group factor. And now if you see, it basically shows us a factor. It does not have any double quotes, and you can also see the factor levels for categorical variables which get printed out here. Now, what actually R is doing here is first R scans through vector to see the different categories in there. Then R sorts levels alphabetically, and then it converts the character vector to a vector of integer values. So these integers correspond to set of character values to use when factor is displayed. Now we can always do a structure to find out more details of this. And here I will pass in blood group factor, and let's look at this one. And this one shows me this factor is with 4 levels. So inspecting the structure will reveal that it has 4 levels. It shows me what are the categorical variables, and it shows me some integers. So here we are dealing with a factor of 4 levels. Now A's are recorded, and A would have, say, recorded as 1, so that would be a first level. You have ABs which are recorded here, and that is basically your second level. B is the third level, and O is the fourth level. So when we are looking at this factor, we may think, why this conversion? So categories could be very long character strings, and each time repeating a string or an observation can take up a lot of memory. So using factors and having these levels can reduce the memory space. Now factors are actually integer vectors, and each integer corresponds to a category or a level. Now to specify a different order of levels, we can specify levels inside the factor function. How do we do that? So let's say I will say blood underscore factor 2, and here I will basically give the same. So I'll say factor, and this factor will have blood group which we had created earlier, but this time also I'm going to specify levels, and then I can basically pass in a vector here. So within these levels I will specify the values. What are the levels? So here I will say O, then I'll say A, then let's say B, and then let's say AB. So this is what we are doing here to specify different order of levels, and we are specifying the levels here. Now if I do this, that would have got created, and let's look at blood factor 2, and that shows me the value here below where you have specifically assigned the levels. Now if you look at the previous one where we had blood group factor where levels were automatically understood by R, so we were looking at the categorical variables, we were seeing what are the levels here, and here what we have done is we have just created again a factor, but then we have specified levels in a different order. And you can obviously do a structure on this to compare. So for example, I'll say structure, and then I will say blood factor 2, and that basically shows me the structure with 4 levels. So this was the initial one where we said A, AB, B, and 0, and then there were some integer values which were responding to these categorical variables. Here we have given a different level, and we have a different set of numbers which we see here. So if we compare structure of blood factor and blood factor 2, we will see encoding is different, right? Now that is done. We can also specify the level names. So what we can do is, as we use names function for name of vectors, we can pass vectors to levels here, and there is basically a function what you can use. So let's say I will say levels, and then within this I'll pass blood underscore factor or blood group underscore factor here. So once this is done, let's say blood group. So in this one we created blood group underscore factor, and this one was blood factor 2, so that's okay. I mean, it's just a naming convention. And here let's pass in levels to my blood factor, and then what I can do is I can pass in the values here. So this is when you would want to give specific names, and let's create a vector and let's call it, say, bt underscore a, and might be you would want to give bt underscore ab, and then you will give bt underscore b, and the final one is bt underscore o. So what I'm doing is I'm doing the naming for these particular categorical variables by using levels. Now let's do this, and it says blood factor not found. So we have to look which one did we have. So we have blood group factor. So this is what we should have given. So let's say blood group factor, and now we have given some names here. So let's look at the blood group factor now. Blood group underscore factor, and now if you see, we have some levels, or we have given the name to the categorical variable. So if you compare this one, so here we were creating a blood group where we had these variables, and these variables were the categorical variables, which was just creating a vector. Then we created a factor out of it, and then we looked at our factor, we looked at the structure of it, and similarly what we did was we created a different factor. So let me also change the name here, and let me call it blood group factor 2, but here we were specifying levels in a different order. Let's look at this one, so which is blood group factor 2, and then you can look at the structure of this one, blood group factor 2. And here in this example what we did was the initial blood group factor what we had created, we have just given some names to that, like what we would do in case of vector by using the names function. Here you're using the levels function. So we basically created some levels, and let's group at the blood group factor now, which basically has some different names. So what we are doing here is we are just using naming. Now we can also specify the categorical variable names or levels by specifying label arguments, so inside the factor function. So that is basically to give some names or levels. So let's look at this one. And how do we do that? So we can specify by using factor, which basically creates your factor. And then here I'll say blood group. I'm going to specify labels for my naming. So in previous examples, we saw how we were using the levels, right? And this was by specifying levels for a different ordering. And then we could have also done this by saying levels and given some different names, or we can just do labels, and then within this I will say labels equals, and then I can say C, and then let's give these values, which we have bt underscore a, bt underscore ab, bt underscore b, and o. So let me just copy this one again, and let's put it here, and then we can basically do a control enter. So I would have created a factor here, and then we should remember one thing here, that it is important to follow in the same order as the order of factor levels, that is A, AB, B, or O. Now these are the levels what we are seeing. So if you look at any one of these in the beginning which we had created, it was showing me what levels it has: A, AB, B, and O, and A, AB, B, and O. So we are following the same order, but we are using the labels within my factor creation. Now, sometimes there might be issues because of wrong ordering. So we can actually use a combination of manually specifying the levels and label arguments when creating a factor. Now, what we can do there is we can say factor, and in this case let's say blood group, which I'm creating. Then I will basically say levels to give the right ordering, and here in levels let's say O, let's say A, let's say B, and then let's say AB. So this is for my levels which I'm creating. And then what I can also do is I can go for labels. So levels will take care of my ordering and labels will take care of my naming the categories. So let's say labels, and then we can create a vector and we can give some names. So we can say bt underscore o. What else we have? We have bt underscore a. We can then say bt underscore b, and finally we can say bt underscore ab. And then let's create this one. So now what we have done is we have created a blood group which has levels, which is following your ordering, which is following the naming as we have passed. So if you look at the levels, it tells you the names what you have created. It also tells you all the categorical variables which were used for my blood group, and basically these will have some labels. So we can anytime look at our blood group which we had created in the beginning, and let's look at the values of those. So when we talk about categorical variables, there are two kinds in categorical variables. So you have nominal or you have ordinal. Now in nominal, you don't have any implied order. For example, blood group O is not necessarily greater than A. That is, O is no or not more worth than A, that we can think of. Now, trying such comparisons with factors will generate a warning. So say for example, we would want to look into our blood factor, and let's look at what blood group factor contains. Now that's the new blood group factor. Let's say blood group factor, and here I will try to pull out a value here, and let's compare this with blood factor, and let's look at some other value. Now in this case we see not meaningful for factors, so it cannot really compare the categorical variables and see if one variable is greater than other or has more worth. Now there can be many examples where such ordering does exist, and in R we can impose such ordering in factors, thus making it ordered factor. So inside factor we can set the argument ordered is true, and we can do that. Now for example, you would look at the size of a dress. So let's say dress size, and here I will say, for example, let's create a vector, and let's say medium, let's say large, let's say small, let's say again small, and then let's say large, let's say medium, again an entry of large, and then let's say medium. So here I'm creating a vector, and let's see if we missed out any quotes or comma. So it says unexpected symbol, and where is that? So let's look at this one. So we have dress size, and we are looking at C. So I'm saying M, L, S, S, L, and here is a quote missing, and that was the reason. So, and this one also has a quote missing. and now it should resolve. Yeah. So let's look at this one. And now we have created a vector called dress size. Now obviously you can create a factor of this. So I'll say dress size underscore factor, where I would want to look at the ordering of this. So let's create a factor, and in factor we will pass our vector on which we want to convert, or we want to create a factor. We will say ordered equals true. So I am specifying a particular ordering, and then I can also specify levels as we saw earlier. So in levels we will give the category. So what categories we have? So we have small, we have medium, and we have large. So these are the three levels which we have, and let's create this as a factor. Now that's done. And what you can do is you can look at the factor, and we can also do a comparison. So let's, for example, look at our factor. What does it contain? It has some levels, and if you closely notice, there are these levels which also have a comparison of which one is worth or more worth than other variable. So you can look at dress size factor, which has some ordering which we have implemented. And now let's do a comparison between dress size and compare it with some other variable and see what is the result. So now it says if it is true or if it is false. Earlier we were not able to do that because we did not have any ordering, and if we were looking at the variables, we were not really clear if one variable has more worth than others. So these are some simple examples what we have seen. Now we can also look at some more examples. So say for example I do a type here. Now that basically is creating a vector. If I would want to compare the element, that is type 3, is it greater than type 4? It shows me false, right? Now here what we are seeing is that if you are looking at a particular value, okay, we can basically see that there is some comparison happening here. If I compare this with 1 and 2, it tells me true or false. And if I look at this, it also does some comparison. So I can always convert this into factor by using the factor function. So I can do this. If I'm checking, if for example I would want to create a nominal factor, I can do a type.factor and it tells me it is true. You can also do a type.factor 2 and then use the factor function, pass in your type, which is a vector, and here you are saying ordered as true, which we just now saw. And now you look at type.factor 2, which is creating an ordinal type of variables. Now here we can again create type.factor 3. So what we are doing here, in this case, we had a vector. We basically said type.factor. We said factor is of true. And then we looked at the nominal factor. We also did a factor 2. And then we created factor, but we specify ordered as true. So we get ordinal. And now if you look at type.factor 3, here you are saying ordered, and you're also specifying levels like what we did in the previous example. And now you would look at ordered factor with user given order, which also has the levels which clearly show us a comparison between those. Now we can take a different example. We can say type.factor 4. We are using the factor function. I'm specifying type, which is a vector. I'm saying ordered is t. I'm using level, which is giving me some levels. And then we also have labels, which are basically going to have the naming convention. So let's look at this one and look at type.factor 4. So it tells me what are the categorical variables, which are small, medium, large, small, large, medium. These are for my type values, which we created a vector here. These are my type values for which we created a vector. We said ordered is true. The levels is small, medium, large, and we gave some names. So we are looking at the values of this. So this basically helps you to work on your categorical variables, wherein you can then compare the values and you can see what does it show. Now here what we are doing is we are creating a different vector. We say small, tall, tallest, medium, small, and so on. Let's look at this one, which is basically type, and it has the value. So what we would want to do is we would want to compare height type of first value with the fourth value. So for that, let's create a vector on this type. Ordered is true. Level is we are saying small, medium, tall, and tallest. These are the levels. And now when you look at your type dot factor phi, it basically shows me what are the levels which you have specified. So small is the smallest, then you have medium, which is bigger than small, tall is bigger than medium, tallest is bigger than tall. We have assigned some levels, and based on these levels, now you can compare your values in this factor type dot factor 5. Take the first value, which is small, and compare it with the fourth value, which is medium, and you will know if small is greater than medium, so the result would be false. Now I can also convert this into integer and I can continue working on this. Now here you have basically a sequence. So let's use the sequence function where I'm starting from 0, ending to 20, and there is a jump of 2. So that basically creates a vector. Let's look at the vector value here. And if you would want to sort the vector, so we are using an inbuilt function wherein let's create this vector with these numbers. I can do a sorting. I can also do a sorting with decreasing is true. You can do a reversing of vector. So these are some examples of inbuilt functions which we have already discussed. So here you are doing a reverse, you are finding out the structure, you want to append two vectors, you want to check the class of an object, you want to convert a vector into a list using as.list, converting the vector into a matrix, you are having a sample with two random values between 10 and 20. So these are some inbuilt functions which we have already discussed, such as your absolute, such as your vector and getting an absolute value, or getting a sum of it, or a mean of it, a round, or basically rounding it to two decimal places, getting the ceiling value, getting the floor value, truncating it, returning the log, getting the exponential value, and so on. Now we have also looked at regular expressions earlier. So regular expressions, let's just revisit that. So here you are basically creating a variable called text, and then you can just do a grep. You can say what you would want to search and where you would want to search it, and that would give you the logical value indicating if the pattern was found. You can try to search something else which might not be found. You can also search for independent values like this, and that basically can give you the position of that particular object within the vector. And here is one more example of working with timestamps. So for example, if I would just do a sys.date, it returns the current system date. If I would want to set that as a variable and then call that variable, it shows me our current time. I can also use as date, and then let's look at this one. So as date, and this would be converted into date. And then you can obviously use formatting techniques like getting the month, getting the day, getting the year. So here we are passing in the date, and then we are saying what format we would be interested in, and that basically gives us the data in a particular format. So that's also useful when you have your time series data, or when you would want to convert the data types and so on. Now there are different ways in which you can do formatting. So for example, in this one we were saying month, day, and year. I can also say for getting the full month name or getting the full year name, I can do this caps. So I can look at this one, and that basically shows me my date in a particular format. So these are some inbuilt functions which we are seeing. And before this, we were seeing factors, which is mainly to work with categorical variables. Either they have levels auto assigned and they might not have labels. So you can give labels, you can give levels, you can control the ordering, you can give levels in a different way so that you can have a different ordering. So this is how you use factors and work on categorical variables, maybe that is nominal or ordinal, and easily you can do your statistical computations on such data. Let's learn about data manipulation in R, and here we will learn about dplyr package. And when we talk about this dplyr package, it is much faster and much easier to read than base R. So dplyr package is used to transform and summarize tabular data with rows and columns. You might be working on a data frame, or you might be getting in a inbuilt R data set, which can then be converted into a data frame. So we can get this package dplyr by just calling in library function, and this can be used for grouping by data, summarizing the data, adding new variables, selecting different set of columns, filtering our data sets, sorting it, selecting it, arranging it, or even mutating. That is basically creating new columns using functions on existing variables. So let's see how we work with dplyr. Now here I can basically get the package here. So I can just say install.packages dplyr. Now we already see the package here, which is showing up. So I will just select this one. I can do a control enter, and that will basically set up the package dplyr successfully unpacked. So that is done. Now you can start using this package by just doing a library dplyr, and this was built. It shows me my version of R. So let's also use a inbuilt data set, that is New York flights 13. So we can do install.packages, and that will search and get that relevant data set. I can again call it by using library function. Now once that is done, we can look at some sample data here by just doing view flights, and that shows me the data in a neat and a tabular format, which shows me year, month, day, departure time, scheduled departure time, and so on. Now we can also do a head to look at some initial data, which can help us in understanding the data better. So what is this data about? How many columns we have? What are the data types or object types here? It shows me how many variables we have. So this is fine. Now we can start using dplyr, and in that we can use, say, filter function if we would want to look in for specific value. Now here we have the column as month, so I will do a filter. Now I'm creating a variable f1. I'm using the filter function on flights, which we already have. And then what we can do is we can basically look at the month, where the month value is 07. So let's look at that. And this one, you can do a view on F1, which shows me the data wherein you have filtered out all the data based on month being 7. So this is a simple usage of filter. We can take some other example. We may want to include multiple columns. So we can say F2 filter flights, and here we will say month is equal to 7, day is 3, and then look at the value of F2 if you are interested in seeing this. And that tells you the month is 7 and day is 3. You could also look into a more readable format by using view on F2, and that gives me my selected result. So we are just extracting in some specific value. We can keep extending this. So here we can say flights is what we would want to work on. I'm using the filter function, so I can straight away, instead of creating a variable then doing a view, I can also do a view in this way. I can just pass in my filter within the view, and within this I'm saying filter. I would want to look at the flights, month being 09, day being 2, and origin being LGA, and then that shows me the value here. And obviously you can scroll and look at all the columns, and if you see the origin column, it shows the selected value. So now we have filtered our data based on values in 3 different columns. Now what we can also do is we can use AND or we can use OR operators. So I could have done this in a little different way. So I could have said head, which shows me initial result. I will do a flights. So within my head function, I'm passing in this. And what does that contain? So you are saying flights. And in this flights data set, you would want to pick up the month being the column. So we use the dollar symbol here. We give in a value and I'll say and I'll again say flights, wherein I will select the day being 2 and remember, when you talk about and, it is going to check if all the values are met true. So then you say flights origin LGA and you look at the value. So in this way I can filter out specifically multiple values by specifying columns. Now we could have done it in this way. We could have created a view, or we could have assigned this to a variable and then done a view on that, where we could have selected month being day and origin. Or you can be more specific in specifying all the columns. It makes the code more readable. So let's look at the values, and here you are looking at head, which shows me based on month, day, and then you can look for further columns for other variables, that is origin being LGA. Now what we can also do is we can do some slicing here to select rows by particular position. So I can say slice, and I would want to look at rows 1 to 5, and I can do this. So you can always assign or look at the view of this. I can just do here. So when I did a slice 1:5, it shows me my entries for 1 to 5. Now similarly, we can do a slice 5 to 10, and now you're looking at 5 to 10 values. So you can always look at the complete data and then you can slice out particular data. Now mutate is usually a function which is used when you would want to apply some variable on a particular data set, and then you would want to add it to your existing data frame, or you would want to add a new column. So this is where you use mutate, which is mainly used to add new variables. So let's see how you work on mutate. So it's pretty simple. So you create a variable over delay. Now I would want to do a mutate so that it adds a new column. So I'm selecting my data, which is flights. I will call the new column as overall delay, and then basically I can look at overall delay being arrival delay minus departure delay. So let's create this and let's look at view of this, which shows me, or which should show me, my new column, which is overall delay, which was not in my original data set. So you can anytime do a head on this one to compare the value. So this one shows me arrival delay, and then there are many other variables. What you can also do is you can do a view, and you could have just look at flights if you would want to compare. So you can look at the flights, and this one would not have any overall delay column. So it basically shows me 19 columns only, what we see here. And if you do a view on overall delay, then that basically shows me 20 columns. So we know that the new column has been added to this overall delay. So if you would want to work with 20 columns, you will use overall delay. If you would want to work with your original data set, you will use flights. Now you can also use a transmute function, which is used to show only the new column. So we can do an overall delay, and at this time we will say transmute, we will say flights overall delay. The computation remains same, but at this time if I look at view on overall delay, it only shows me the new column. So sometimes we may want to compute result based on 2 variables or 2 columns and just look at the new value, and then we can decide if we would want to add it to our existing structure. Now you can also use summarize, And summarize basically helps us in getting a summary based on certain criteria. So we can always do a summarize, and what we can do is we can look at our data and we can say on what basis we would want to summarize this particular data. So we can do a summarize function. Now summarize on flights, I will say average air time, and I would want to calculate an average. So for that I'm using an inbuilt function called mean. I will do that on airtime column. So let's look at flights once again, and here we can see there is arrival time, not airtime, sorry, arrival time, and we would want to do some average on this particular data. We would want to summarize this. So what I'll do is I will use the summarize function. I will say average airtime, and this one I will look at mean of airtime. So let's see if there is a airtime column. I might be, let's look at this one, arrival delay, and yes, we have an airtime. So we were actually looking at summarizing based on airtime, not the arrival time. So airtime is how much time it takes in air for this particular flight, and we will want to use the summarize function, not the transmute. So summarize flights average airtime, and this one we will calculate the mean of average airtime, and I will also do a NA removal, which is I'm saying true. So let's do this, and that basically shows me the average airtime is 151. I can also do a total airtime where I'm doing a summation of values, or I can get the standard deviation, or I can basically get multiple values such as mean. I can say total airtime where I'm doing a summation, and then I can look at other values, which is if you would want to put in standard deviation here, you could do that. So let's look at the result of this summarize, and this basically allows me to get some useful information which is summarized based on a particular function such as mean, sum, standard deviation, or all three of them. Now let's look at grouping by. So sometimes we may be interested in summarizing the data by groups, and that's where we use the group by function. So we can always use the group by clause. Now here we are taking a different data set. So we will say, for example, let's look at head of empty cars, and that is basically my data set on empty cars. Now that shows me the model of the car, it shows me mileage, cylinder power, and your horsepower and various other characteristics or variables in this particular data set. So here we can say let's do a grouping by gear. So there is a column called gear, so I will call it by gear. I will look at my data set, and then what I'm using here, which you see with these percentage and greater symbol, is called piping. So that basically feeds your previous data frame into next one. So this is sometimes useful, and you can get this by just saying Control Shift and M, and you can then use this. So we are going to have piping. So I'm saying empty cars. Now this is my original data set where I did a head, or I could have done a view on this one if you would want to see it in a more readable format, and that basically shows me the data. So we are using a different data set, so I want to group it by the gear column. So I'm going to call it by gear, and this one takes my data that is empty cars. I'm using the piping, and then I'm saying group the data based on gear column. That's done. Now let's look at the value of by gear, or you can always do a view. So remember, whenever you're doing a group by, it is giving you a internal object where your data is grouped based on a particular column. So we can look at the values here. You can do a view that shows you your data grouped based on a particular column. Now I can again use the summarize function where I would want to now work on the new one where it was grouped based on gear. So I'm doing a summarize, and here I'm going to say gear 1, which will be having the value of summation on the gear column. and then I'm saying gear2, which is mean. Well, you could give some meaningful names to this, and let's look at the value of this one, where we are basically now looking at the values, which is sum and mean values based on the gear. Similarly, we can look at different example. So we can say by gear, and I'm again using piping, but earlier we had taken gear, we had grouped the data, and we called it by gear. So we took our original data set empty cars, but now within this particular data, which was grouped by gear, I will take this data set, I will use the piping, and I will summarize it, where I am saying within this particular data set, I would want to get the sum, or I would want to get the mean, and then you can look at the values. So what you're doing is you are either looking at your original data set, or you're looking at the data which was already grouped, and then you can look at the values. Now here, what we can do is we can group by cylinder. Say might be you are interested in looking at data which is summarized based on the cylinder column. You can do that. And then for this by cylinder, I'm doing a piping where I'm using the summarize function, and summarizing will then be done based on the mean values of the gear column or the horsepower. So let's do this, and then you can basically look at the value. At any point you may want to look at the data set again, so just do a head and you can look at what does the value contain, and by cylinder or by gear, and do a head, and it gives you the value. So you can always do some summarizing or grouping in these ways. Now here we are going to use sample underscore n function and sample underscore fraction for creating samples. So for this, let's take the flights data set again, and we would want to get 15 random values. Now that is done, and it shows me 15 rows with some random values from the data. What you can also do is you can do a portion of data by using sample underscore fraction, and here I'll say flights, I'll say 0.4, which will return 40% of the total data. So this can be useful when you're building your machine learning, where you would want to split your data into training and test. Might be you are interested in some portion of the data, so you can do this, which is very useful function, and then you can look at the value of that. Now what we can also do is we can use a range function. So like we were doing a grouping by, or we were trying to pull out a particular column. So in the same way, we can use a range, which is a convenient way of sorting than your base R sorting. So for a range function, let's do a view based on a range. So we will work on the flights data set which we have, and here what we would want to do is we would want to arrange the flights data set which is based on year and departure time, and we are doing a view out of it. So that basically gives me the data which is arranged based on your year and departure time. Now I can do a head to give me some highlighting of that data. Now the piping operator, what we are using, can be used in these ways also. So here I will say df, I will just assign the data set empty cars to it. Let's look at the df, which has basically your different models. You can obviously look at the head or view of it to look at useful information. We can also go for nesting options, which can be useful. So we are creating a variable called result here. Now that has the arrange function. So what does this arrange function do? So when we would want to use arrange to sort the data, so I would want to sort the data, but what data would I sort? So I will use sample n, which will give me some portion of the data or some sample data. Now what is that sample data? So here we are using nesting. That is, earlier when we did a sample, we just said data and how many random samples we want. But instead of giving that, what we are going to do is we are going to use filter here. Now this filter will work on df. So filtering will happen based on the mileage, which is greater than 20. I will say size is 5, and I would want to basically arrange this in a descending order. So I'm using the des on this particular mileage column. By default, it is always ascending. So let's get the result out of this, which will basically show me the mileage details in a descending order. So this is my data frame, and now we can look at the result, what we have created. So just do a view or do a head and look at the view. So here you see mileage, where the highest value is on the top, and we were only interested in 5 values in our random sample. So that's why when you did a view, it shows your 5 values, and it shows in a descending order based on mileage. So we have not only used an inbuilt function, we have not only arranged the data, that is, we have sorted the data, but we have sorted the data based on a descending order on a particular column. We have said the value should be greater than 20, and we have also said we just need 5 random samples. Now let's look at some other examples. So you can always do a multi-assignment. So I can say filter, wherein I'm going to use DF, which was assigned empty cars. I'm going to say mileage should be greater than 20. Then I say B, which is going to get a sample out of A, and I just want 5 random values. So let's look at that. So we have B, which is going to get a set of 5 values from A. Now I will create a result variable which will arrange B, which is sample data, in a descending order. Now let's look at the result of this, and that basically shows me what we were seeing earlier. So you can do a multi-assignment where you can create a variable, get a sample out of it, and then basically whatever is that result, you can arrange that or sort that in a descending or by default ascending order. So same thing, we can do it using pipe operator. So piping. So here I will say result. I'm passing in my DF, that's the data set. I'm using piping, and which basically tells what you need to do on this particular data set. So I'm going to filter out the data based on mileage 20. Then I'm going to push that or forward it to get the random sample, and whatever is this random sample is going to be pushed. So you are arranging this in a descending order. So this is one more way of doing it, and then basically you can look at the result. So these are some simple examples where you can use your dplyr with multiple assignments, or using your nesting to filter out the data. You can also do a range, which is to sort the data. You can get some random samples out of it. You can summarize the data. You can also summarize the data based on 1 or 2 or multiple columns, and you can use some inbuilt functions to summarize the data based on some functions which are applied on the variables or on the columns. You can transmute it, where you would be interested in only looking at one column. You can mutate it, where you want to add a new column. You can slice it, and you can give the conditions where you can say and or to filter out the data. So what we can also do is, on this particular data set which we have, say for example DF, where I have my data, let's look at this one. And if I just do a DF at this point, it shows me my data set. And if you would be interested only in particular column, then your dplyr also allows you to, either we can do a filter or we can simply do a select. Now for selecting, we can choose our data. So for example, I'll say df underscore, I'm interested in mileage, I'm interested in horsepower, might be I'm interested in your cylinders in this. And for this one, what I can do is, when I would want to do a select, I can basically say selected df, let's call it some name. I can say Control Shift M, which is for piping. And then basically what you can do is you can do a select, and you can choose your columns. So I was interested in mileage. I was interested in horsepower. I was interested in cylinder. And here what I'm doing is I'm using a select where I can look at the new data frame. So let's do this. And I'm sorry, here we will have to give it df. This is where you are passing in your data. Yeah, now this one is done, and we can look at the value of this one by just doing a df or head on df underscore mileage horsepower cylinder and look at the selected result. So you can be looking at selective columns. I could have done this filter, but filter will always look for a condition. Say your mileage is greater than 20, or might be your cylinders are more than 4 or something else. But when you do a select, you are selecting specific columns. So view always gives you all the columns, head gives you highlight, but then select can be useful when we are interested in looking at only specific data. So this is how you can use dplyr for manipulation, for your data transformation, for basically filtering out the data by selecting particular data and then working on it. So similarly, there is one more package called tidyr, and we'll see how we can use data manipulation done using your tidyr package.
Let's learn about the tidyr package, which makes it easy to tidy your data. And this basically helps you creating a more cleaner data, so which is easy to visualize and model. Now this comes with mainly 4 functions. So you have gather, which makes your data wide, or it makes wide data longer. So that is basically used to stack up multiple columns. You have spread function, which makes long data wider, that is stacking the data together, or stack if you would want to unstack the data to data and you are talking about data which has same attributes. And then your spread can spread the data across multiple columns. You have separate, which is function which splits single column into multiple columns. And to complement that, you have one more function which is unite, and that combines multiple columns into single columns. So these are 4 main functions which are used in your tidyr package. So let's look how we work with this. So let me bring up my R Studio here. Now for this, first is, let me just clean up my screen here, doing a Control L. So I will install the package. It is already installed, but we can just do a Control Enter. And then I can say, do you want to restart R prior to reinstall? So install, I'll say okay. And it is basically going to get the package. Now it says package TIDYR, that is tidyr, has been successfully unpacked. Let's use that package using our library function. And that was built under R version 3.6. Now I can basically start using these functions. So for example, here we are creating a data frame. So let's say n is 10. And then we basically would say, we will call it wide. Now that's the variable name. I'm using the data.frame function. I'm saying ID, which will be 1 to n. So that will take the values from 1 to 10. And then these are the values which have 10 entries. So this is a vector, phase 1, phase 2, phase 3. Let's create a data frame out of it. Now that's done. We can have a look at our data frame by just doing a view wide, and that shows me the ID column, and it has phase.1, phase.2, and phase.3. Now we can use our function. So for example, we can work with gather, that is reshaping the data from wide format to long format. And basically you can say stacking up multiple columns. So let's see how we do that. Here I'll call it long. I'm working on wide. I'm using the piping functionality, and then I'm using gather. So this one, I will say what will be the data which I will use. So we are using wide as a data frame. Then I'm saying response time. So that will be basically one more column. And then you have your columns which you would want to basically stack. So I'm saying from phase 1 to phase 3. So let's do this. And once this is done, let's have a look at our variable long. So this one shows me that I have an ID column, I have the response time column, and I have the face column, which we mentioned, and that basically has all the values stacked in. So you have face.1, face.2, and face.3. So all the columns are being stacked here. So all my data, so now I have totally 30 entries in this one. So this is basically using your gather function. Now sometimes we may want to use a separate function. Now separate function is basically splitting a single column into multiple columns, so which we would want to use when multiple variables are captured in a single variable column. Okay, so let's look at an example of this one. So let's say long separate, that's what we will call. We will work on this long, which has all the data stacked in as the columns we selected. Then I'm saying separate, I want the face column, and then I would say when I separate the columns, what are my column names. Now I could also give a separator by giving a comma and then mentioning the separator if that is required. So let's do this. Now once this is done, let's have a look at our long separate. So what we see here is the column which we used. So we were doing a face column, and that was to be split, and we wanted to split it into target and number. So that's what we see here. So you have face being split into target and number, and then you have the response time. So this is how you use the separate function. Now there is also something called as unite function, which is basically a complementing of separate function. So it takes multiple columns and combines the elements to a single column. So for example, here we will call it long unite, and we will take long separate, which was separating the data. We want to unite, so we will take face, target, number, and we want to have a separator between them. So let's basically do this. And now let's look at the result of this unite. So you see, you have the face and target merged together. So you have face.1, the separator is dot as we have mentioned, and we have united multiple columns. So this is one more function of your tidyr, which helps you basically tidy up your data or put it in a particular way. Now then you have your spread function, and this is basically for unstacking. So that is, if you would want to convert a stack to data, or if you would want to unstack the data which is of same attributes, spread can be used so that you can spread the data across multiple columns. So it will take two columns, say key and value, and spread it into multiple columns. So it makes long data wider. So we can look at this one. We will say long unite. I'm using the piping. I will use the spread function. I'll work on the face column and response time. And let's do this. And then let's do a view on this. So it tells me our data is back in the shape as it was in the beginning. So these are four functions which are very helpful when we work with tidyr package.
So let's learn about visualization. And here we will learn about R, which can be used for your visualization. Now, one thing which we need to understand is, because of our ability to see patterns, which is highly developed, we can understand the data better if we can visualize it. So the efficient way or effective way to understand what is in our data, or what we have understood in our data, we should or we can use graphical displays, that is your data visualization. So there are actually two types of data visualizations. So you have exploratory data visualization, which helps us to understand the data, and then you have explanatory visualization, which helps us to share our understanding with others. So when you talk about R provides various tools and packages to create data visualizations, and which can be used for both kind of data analysis or both kind of visualizations. So when you talk about exploratory data visualization, the key is to keep all the potentially relevant details together. Now, the objective when we talk about exploratory data analysis is to help you see what is in your data. And the main question is how much details can we interpret? Now, when you talk about different functions which we see here, such as plot, which is more for a generic plotting. You have bar plot, which is used to plot data using rectangular bars, or you can say creating bar charts. You have histogram or hist function to create histograms, where you look at the frequency of the data, or basically used to look at the central tendency of the data. You have box plot, which is used to represent data in the form of quartiles. You have ggplot, which is a package which enables the user to create sophisticated visualizations with the little code using the grammar of graphics. And then you have plotly or plotly. It creates interactive web-based graphs via the open source JavaScript graphing library. Now, before we see some examples here, let's also talk about, when you talk about plotting, let's also try to understand what kind of plots you can have and what kind of techniques you have. So let me open up my RStudio here. Now, for example, I can pull out a particular data set, and let's look at this one. So here I can look at all the panes, and that shows me the information. Now what I can do is I can install and get the inbuilt datasets, and then I can simply do a plot wherein I am doing a plot on chick-weight dataset. So let's see what does that show. It summarizes the relationship between 4 variables in chick-weight data frame, which is in R's built-in dataset package. Now from these plots, we can see, for example, weight varies systematically over time. You can also see that chicks were assigned to 4 different diets. Now, when we talk about explanatory data analysis or visualization, that shows others what we found in the data. This means we need to make some editorial decisions, what features we would want to highlight for emphasis, what features are distracting or confusing and you want them to be eliminated, right? So there are different ways of doing it. Now, when you talk about your graphics or visualizations, you have, I would say, 3 different types, or you can say 4. So you have the base graphics, which is easiest to learn. Now here we are having an example of base graphics, where I can use the base graphics. I can get a data set using library. Then I can simply create using plot function to generate a simple scatter plot of calories with sugar from US serial data frame in the mass package, and then I can give it a title. So this is basically a simple example of base graphics. Now you also have what we call as grid graphics, which is powerful set of modules for building other tools. Now you also have lattice graphics, which is general purpose system based on grid graphics. And then you have your ggplot2, which implements grammar of graphics and is based on grid graphics. So you have different ways. Now here, since I already have used library and I have the data set, I can just do a X. So I can assign the sugar related values to X and calories related value to Y. Then I can use one more, which is library function and calling in grid. Now I can basically use functions such as push viewport if I would want to create a plot using your grid graphics to create the similar kind of plot which we created using base graphics, but this will give you much more power than base graphics. It will have a steep learning curve, but it is usually useful. So I can do this where I'm saying push viewport. Then I can basically say I would want to have a data viewport. I would say different functions of your grid package. So I'm saying rectangle, you have x-axis, y-axis, given some points here. And then basically you can add details to the graph by giving the names to the columns, and you can basically create a simple grid graphics based plot here. Now there are different other options which we can use to create plots. Now, before we go into understanding how you create plots, let me just give you a brief on what are the different kind of plots and how they can be used. So here we will look at these different plots. Now, for example, we have a bar chart, which is a graph which shows comparisons across discrete categories. So you have x-axis, which will show the categories being compared, and y-axis, which represents a measured value, and height of the bars are proportional to measured values. Now, to create different kind of charts, you can use ggplot, which is a package for creating graphs in R. It is basically a method of thinking about and decomposing complex graphs into logical subunits, and that is a part of tidyverse ecosystem. So it takes each component of graph axes, you can give scales, you can give colors, you can give the objects, and you can build graphs on particular data. You can modify each of those components in a way that's more flexible and user friendly. You can, if you are not providing details for the components, then ggplot will use sensible defaults, and this basically makes it a powerful and a flexible tool. Now here are different options when you use your ggplot, such as you can use geom, or what we call as geometry objects, to form the basis of different type of graphs. For bar charts, you have for line graphs, you have scatter plots, that is underscore point, you have underscore box plot for box plots, you have quartile for continuous x, violin for richer display of distribution, and jitter for small data. So here is some simple example where I would not go into too many details here, but you can just have a look at this one where we are using library function to get the ggplot2 package. Then basically we would want to look into the mileage data. We would want to look at the structure of it. And then we can basically get the tidyverse package. Finally, we can create a bar chart using geom underscore bar, and we can basically also mention what would be in x-axis. Now you can also give different colors to basically add more meaning to your data. You could also go for stacked bar charts. So here we are actually telling ggplot to map the data in the drive column to fill the aesthetic. So here I am giving aesthetic access class, and I'm saying what is the data we need to have, and then we are using geom underscore bar. So you can also have dodged bar in your ggplot, that is not bar charts which are stacked but next to each other, and you can create that by using your position as position underscore dodge. Okay, now you can obviously use your different packages which are inbuilt, and you can create your bar charts. And you have other kind of graphs such as line graph, which is basically a type of graph that displays information as a series of data points connected by straight line segments, such as this one. And for this one we are using, if you see, geom underscore line. Now you can also create a scatter plot, which is a two-dimensional data visualization that uses points to graph the values of two different variables, one on an x-axis, one on y-axis, like what we saw in base graphics example. And they are mainly used if you would want to assess the relationship or lack of relationship between two variables. And you also have histogram, which I mentioned is mainly to look at the distribution of a data, to look at the central tendency of the data, basically looking at your large amount of data or for a single variable. You would be interested in saying where is more data found in terms of frequency, where is lesser data found in the graph, how close the data is towards its midpoint, or what we call as mean, median, mode. So you can use histogram where you can categorize the data in what we call as bins. So these are some basics on different kind of graphs. Now we can look at some examples and see how that works. So what we were seeing is some quick examples of base graphics or grid graphics. Now here, let's do an example of pie chart for different products and units sold. So you want to create a graph for this. First, let's create a vector and pass in the value here. Now I can also create labels which I would want to assign to these values. And then basically I can plot the chart by saying pi. So that's the kind of chart which I would want to create. And I would say the data would be X and labels. So let's do this, and that shows me a simple pie chart. Now I can also give main details here. So instead of just doing a pie X comma labels, I can say what is the main and then what kind of coloring it should follow. So this is the way you can create a simple plot. Now I can also find out what is the percentage, and then basically I would be interested in plotting the pie chart which takes X, which takes the labels, which will be the percentage which we are calculating here by doing a round function. And then you can basically give details to your graph. You can say what color it follows. You can basically look at the legend where it needs to be in your chart. What are the values? And then basically fill up the colors. So let's run this one, and that shows me the percentage which was calculated, and it gives me the details, and we can always have a look at our plot. Now if you would want to go for a 3D pie chart, then you can get the package which is Plotrix. Let's use that by calling in the library function. Let's pass in some data to X, and let's give some values or labels which will make more meaning to the data. And then let's plot the 3D graph. So I'm saying pi 3D here, where I'm using X and labels. Then I'm basically doing an explode, which will basically control how your graph looks like and basically give the values. So it also takes the title when you say main and pie chart of countries. Now let's create data for graph. So again, we are having a variable here. We are using the C function, creating a vector, and then let's create a histogram for this one, where I would say xlab, what would be your data around x-axis, what is the color, what is the border, and here I'm creating a simple histogram, which, as I discussed earlier, will always show your values on the x-axis, and y-axis is more of frequency. And then you can look at the set of values and what is their frequency. And we can basically use this histogram for exploratory data analysis, look at the data, try to understand what is the central tendency of your data values. Now we can also give some limits by using the xlim and ylim, and then I can also specify what is the limit. So we have given some values here wherein we have said your x limit is 0 to 40 and y limit is 0 to 5. Now if you compare this with the previous one which we had created, this one based on the frequency had taken the limits, but we can assign limits explicitly by giving this and then create a histogram which makes more meaning. Now let's take another data set, that is air quality. Let's view this to see what does that data contain. So you have ozone, solar, wind, temperature, month, and the day. So this is the kind of information we have in the air quality. Now let's use the plot function to draw a scatter plot, where, as I mentioned, you would be interested in analyzing variables and see what is the relationship between them. So to plot a graph between ozone and wind values, so we will say plot, we will say the data which is air quality. From that I would be interested in the ozone column or ozone field and the wind field. I can create a plot based on this. Now I can also be saying what should be the color, what is the type of the data which you would want to create, and you can look at the information. So you can create a histogram, you can create a scatter plot to basically understand the data better and then infer some information from that data. So let's take the air quality data set itself without specifying any particular column, and you can create a plot which shows me all the different values which you have in the data, and it basically shows you the difference. This is more of an example like what we did for chick weight, where we did a base graphics. Now you can assign labels to the plot. So that is when you are creating a plot, you can say air quality, you will say ozone, and then that's your ozone concentration. You have your YLab, which is the number of instances. You have what is the title, ozone levels in New York City, what is the color. So these are the details what we have given with our plot function. And let's look at the data. So it just tells me that this is the ozone concentration, the number of instances what you have, and you are looking at the data. Now we could also create a histogram by picking up a particular column that is such as solar from your air quality, and that basically shows me the frequency of solar values, and we can then try to find out what is the mid, what is the mean, what is the standard deviation, and so on. You can also look at your histogram and try to understand if it is left skewed and right skewed. So we can do that. Now here, let's get the temperature out from this particular data set. Let's create a histogram on temperature, and that basically shows me the frequency of the temperature values and what values have the most frequency or most occurrence. Now you can create a histogram with labels. So let's do that with the limit, and then let's also use text to basically give in the values, which also takes the values, and for each set of frequency or each set of values it gives me the labels. Now you can have a histogram with non-uniform width, so you could do that by doing a hist function and then passing in your temperature. You can say what will be the main, what is the title, what will be your xlab. It will tell you a limit around x-axis, what is the color, what is the border, what are the breaks you would want to have for your bars, and you can simply create a histogram using this. So this basically takes the breaks which we have given, such as 55 to 60, 60 to 70, 70 to 75, and so on. So this is basically creating a histogram with non-uniform width, and it purely depends on the kind of values what you have. Now you can also create a box plot, which sometimes helps us in understanding the data quartiles, also understanding our outliers. So you can create multiple box plots based on the data from air quality. So we'll select all the data and then we'll do some slicing on the data. So let's create a box plot which tells me the values, and if you look at these points here like single dots, these are basically your outliers. We can learn about that more in later sections. So you can use your ggplot2 library to analyze a particular data set. So for that, we will first use the install.packages and get ggplot2. So it says, do you want to restart R? And I can say yes. So let it get the package. I think the package was already there. And now let's look at using ggplot2. So for that, I have the library function, and let's do a attach where I'm getting a data set which is empty cars. Now then I will create a variable p1. I will use ggplot. I will pass in my data. I'll give the aesthetics, what is the columns which you would be interested in, and then you are using geom_boxplot to basically create a plot which gives me the box plot for the values here, and this is based on the cylinders which is there in your data. So we can always look at what does our data contain and what kind of values or features are available in the data. Now let's create a box plot. We will also use the coordinate function, and that basically gives me based on the data. So I've changed the coordinates. Now if you look at the previous one where we created a plot, we had mileage on the y-axis and cylinders on the x-axis. Now I did a coordinate flip, and that's like your transpose function. So you have created the box plot, but you have just flipped the coordinates. You can create a box plot and then say fill, which is the factor of cylinder. So that can be used to fill up the values in your box plot. Now what we can also do is we can create factors. So we have learned about factors earlier, which is usually used to work on categorical variables. So here let's create a factor which is empty cars, gear, you have AM, you have cylinder. And if you look at the factors which we have created, we have passed our data. What is the field or the column we are interested in? What is the level of values there? And what are the labels for those values, right? So we have learned about factors. You can always look into the previous section and learn more about factors. Now let's create a scatter plot by using the ggplot function. Again, we will use the data as empty cars. I will go for mapping option, and then I will give my aesthetics. That is what would be X, what would be your Y, and you also would want to use what kind of function you are using. So let's go for geom point, and that basically helps me in creating a scatter plot. Now you can create a scatter plot by factors. So here we will say ggplot. So notice in all of these cases, depending on the kind of data you have, depending on the kind of plot you are interested in, you will use the ggplot and then basically a function with that or the inbuilt package. So here I'm saying data is empty cars. I'm going for mapping, which basically will take the values for your X and Y. What is the color? And the coloring will be done based on the factor values. Now, if you remember, factors will obviously have some levels, and those levels will basically help you in differentiating between your categorical variables. So I'm saying as.factor on cylinder, and then I'm using geom point to basically create this scatter plot. So let's do this, and I can look at the values of this one. So it says must be, there is an error which says must at least one color from the hue palette. So let's look at that one. So the error which we were facing when we gave color as the factor values was because when you look at these factors which were created with some labels, if we look at the values of these, it tells me there are any values in that particular column. Similarly, your gear, or similarly, you can completely look at the complete data set. It tells me cylinder, you have AM, you have gear. Now these have some, we have created some labels, but these have NA values. So what we can do is we can create a scatter plot as we did earlier by giving the aesthetics, and that's a simple scatter plot wherein I'm also using geom point so that I can have these points by defaults or with defaults. You can also give a color specific, basically if you would want to have different kind of data in the same plot, or I can create scatter plots by different sizes by giving a size, or I can give a color and size, and that's again one way in which you can create your scatter plots. Now let's also see how you can visualize one more data set, which is MPG. So I can also do it in this way where I set ggplot2 and then pass in, look at the data set what we have here. You can just do a view on this to see what my data contains, if the fields have any NA values, if that's going to affect your plotting. So now what we can do is we can create a bar plot or a bar chart. So I'm saying ggplot, the data would be as we have given in previous lines, that is ggplot2 mpg. Then I will say what should be in my aesthetics and what kind of chart are you going to create. So I'm saying geom underscore bar. So that's my bar chart, and that has basically your class and count. Now you can create a stacked bar chart where your information is stacked in the same bars, and we are still using the same data. We are going for aesthetics, which is class, and then when you say geom bar, which creates your stacked bar, we will use fill, which is drive. And we can always go back and look at our data. For example, you can always look into this. So you have the drive column here, and you are also working on this complete data set. So let's go ahead and create a stacked bar chart. And that basically gives me the information where you have the drive information, which is stacked here. Now you can do a dodge by giving the position as dodge. So we are still going to go for a stack chart, but this time the bars will be next to each other, and that can also be done, which is very useful. You can use this by using geom point where you are mapping and you are specifying what are your aesthetics. So we were creating a scatter plot. Now you can also use or give more details where you can say color can be based on the class, and we have different classes, and based on that my points have been colored. Now you can also use a plot ly or plotly library. So let's install this one. I will say yes, for example. Let it basically restart so that all my packages are updated. Then I can access that package using library function, and then create a variable to which you are assigning your plot underscore ly plot. So data is empty cars. What will be your x-axis, what will be your y-axis, and details on your marker which we have given, wherein I will give a list which is size, color, which is a combination, and then you have your line, what kind of color it will have, and what will be the width. So this is where I'm going to use plot ly, and let's look at this plot. So it basically gives me some information. Now we see some warnings which are getting generated, but you don't need to worry about that. So you can look at the packages, what you have, and what options you are using. So similarly, we can create one more plot using plot ly and look at the values of those. So that's a plot with a trend which explains me about my data. So this is a simple small tutorial on understanding or how you can have your graphics or visualization used to understand your data. Obviously, there are much more examples, much more ways in which you can pass into your plot functions or your ggplot and the inbuilt packages which are available in R for your visualization. Now that could be for exploratory data analysis or explanatory data analysis. So try these graphs and see if you can change these options and try or create new visualizations.
Now, let's do a hands-on project to perform a time series analysis using R programming. In this project, we'll be using time series energy data to explore the variations in electricity demand and renewable energy supply over time. Over to Ajay now.
Welcome to this session where we will learn on time series analysis using R programming language. So this is basically a mini project where we will look at time series data and how we can analyze it, visualize it to basically find some important information or gather insights from the data. Now, when you talk about time series analysis, time series is basically any data set where your values are measured at different points in time. So when you talk about time series data, data is usually uniformly spaced at a specific frequency. For example, hourly weather measurements, you have daily counts of website visits, monthly sales total, and so on. So when you talk about time series, that can also be irregularly spaced and sporadic. For example, timestamp data in computer systems, event log, or history of 9/11 emergency calls. Now, when we work with time series data, for example, here I'm taking an energy data set, we can see how techniques such as time-based indexing, resampling, rolling windows can help us explore variations in electricity demand and renewable energy supply over time. Now, here we will look at some aspects of this data set which I am considering. So this is open power systems data set, and here is the data set I have. We can look at the data set. Now this is in a simple format. It has time. It basically has values for consumption, and then you have data for wind and solar and wind plus solar. So in certain cases you have only the date and the consumption, but then if we scroll down, we will also find data for wind, solar, wind plus solar, and so on. So this is a time series data set which we would want to work on. Sometimes you may also have the data collected which just does not have the time, but it may also have timestamp. That is, it would have, say, hour, minutes, and seconds, and that can also be worked upon. So let's consider this data set and let's work on this project where we will analyze this time series data set. Now here we can work on this time series data. We can basically create some data structures out of it, such as data frames. We can do some time-based indexing. We can visualize the data. We can look at the seasonality in the data, look at some frequencies, and also do some trend detection. Now, when you talk about this data set, it has electricity production and consumption, which is reported as daily totals in gigawatt hours. And here are the columns of the data, which I was just showing you. So you have data, you have consumption, you have wind, you have solar, and wind plus solar. So this is the data we have, and we will basically explore, say, electricity consumption and production in Germany, which has varied over time. So some of the questions which we can answer here is, when is electricity consumption typically highest and lowest? How do wind and solar power production vary with seasons of the year? What are the long-term trends in electricity consumption, solar power, and wind power? How do wind and solar power production compare with electricity consumption, and how has this ratio changed over time? We can also do wrangling or cleaning of this data or pre-processing of data and create a data frame, and then we can visualize this. Now let's see how do we do that. So I will open up my RStudio and let's look at the data set. So here is the data set. Now I'm picking it up from my machine. You can also pick it up from GitHub. So all the data sets or similar data sets can be found in my GitHub repository. And here I can look in the data sets. You will find a lot of different data sets here. There are some time series data sets such as power. I can search for power, or you have basically coal, or you have this OPSD Germany daily data set, and there are many other data sets which you can work on. Now, to get the documentation on this project, you can also look in my GitHub repository and you can search for repositories, and then basically you can look in data science and R, and here there is a project folder where I've given the documentation, sample data set, and also your time series analysis related document. This is also the code which you can directly import in your RStudio, and you can practice or work on this project. So let's see how does that work. So first thing is, we will create a data frame from this data set. Now here, if you see, I am using header as true so that it understands the heading of each column. I'm also giving row.names and I'm specifying date. So there is this date column in the data set as I showed you earlier. Let's look at it again. So you have date, consumption, wind, solar, wind plus solar. So you can suggest that date should become the index column, which can be useful. So you can do this. Now let's just create this. Let's look at what does this data frame contain. And here, if you see, it shows me some data which has been now as a part of this data frame structure. It starts with consumption, wind, solar, wind plus solar. And if you see, this one is becoming my index column. So I can always do a head and look at part of the data frame using head or tail. So look at the first records. So let's see this. Now that shows me the head data. I can also do a tail and look at the ending values. So if you closely see here, we have wind, solar, wind dot solar, and that basically has NA values. So there are missing values, but let's look at the tail, and that tells me that there is some data available for wind and solar and wind solar. Now we can always look in a tabular format using view, and we can look at the data. So this shows me that there are values in these columns. We see NA values, but if I really scroll down, I can see some values which would be available for wind and solar and wind solar. So I can just use view. Now I can look at the dimensions of this particular object, and that tells me there are 4,384 rows and 4 columns. You can always look at the structure, that is, check the data type of each column, which can be very useful. So if I see here, I don't see the date column, because date column was considered as an index which can be useful, but I also look at my other columns. So they are of the num types. So that's the data type for each attribute or each column here. Now we would be interested in looking at this date column. So let's look at the data type of this date column. Now if I try to do this, this will show me that this is null because date as a column does not exist because we created it as an index. So if I look at row names and then I search for my data, show me the index column or row dot names, it tells me these are the values. That's the date column which we are seeing here. Now we can access a specific row by just doing a my data and give the index value or row name value. So let's look at that, and that shows me based on this index you're looking at the value. You can obviously search for a different date, something like this. You can also pass in a vector and you can give range of values. So that is 0, 1, 2006 to 4 of January. And we can look at this one. So it shows me these are the values. So here actually I'm not giving a range, but I'm just selecting multiple values from row dot names. Now we already know that in R you have a summary function, so you can always do a summary, and that gives you for each column, it gives you minimum, first quartile, median, mean, third quartile, and maximum values. So we are looking at consumption, we are looking at wind, solar, and wind dot solar. Now this is good, but then if I would want to really visualize the data, access the data, do some analysis, then it would be good to take all the columns, and then we can later decide to change the data type of say date column if we want to use it. So earlier I was using date as row dot names or the name of the rows or index, what you call in any other programming language. So here I will just use my data set and I'll say header as true. I'm calling it my data 2. Let's look at the data, and this one shows me 5 columns, wherein my first column is the date, consumption, wind, solar, and so on. Now looking at the structure, so let's look at the data type. So it tells me that if now I'm interested in looking at the date column from my data to data frame, it tells me it is a factor with 4384 levels, and these are the values. So it is not in a date time format, it's a factor. Now what we can do is we can convert this into a date format. How do we do that? So let's have a variable x, and I'm going to use as.date function, and I'm going to pass in my date column. So that's assigned to x. Now let's look at the head of x, and it shows me the values. We will also see what kind of class it is, and we will look at the structure of x. So class already says it is date type, and look at the structure, so it shows me the format. Now we have converted this column or column related value into x. Now how do I basically extract values out of it or make it a part of data frame? So first I will use, so all once it has been converted in date format, I will go for as.numeric, and here I will create a variable called year, and I will just do a format on x, which is basically of date type, and then I'm saying %y, so that will get me the year component out of this. Let's look at the values. That shows me year component. Now similarly we can get the month out of this, and then basically look at the month values. We can get the day out of it, and we can get the day component. Now if I look at my data 2, which we had created earlier, this basically had date, consumption, wind, solar, wind, solar. So what I can do is I can add these extracted columns such as year, month, day to my data frame using a cbind, that is column bind, and I will assign it to my data 2 again. So let's do this, and now if you look at head, it shows me date, so that should be date format, consumption. Now this one might not be date format, but we'll see. you have consumption, wind, solar, and we have extracted the year, month, and day, which can help us for group by. We can do some aggregations, we can do a plotting, and we can do various things by these additional columns. Now let's look at first 3 rows here. So I'll say 1:3 for my data 2, and that shows me some data here. You can always do a head and look at the sample of data. So that basically shows me month, day, your columns, and then you have your date. Now, what we can do is we would want to visualize this data. We would want to basically understand the consumption. Now, as I said, if we want to visualize the data, say for example, I want this, which is consumption of data over years. And this one is in terms of gigawatts per hour, as we were mentioning here, gigawatt hours. So if I would want to create this visual to basically understand the pattern of the data, how do we do it? So we can create a line plot of full time series of Germany's electricity consumption using the plot method. Now, how do we do that? So here, one of the option is I can straight away use the plot method. I can then say what would be in my x-axis, what would be on my y-axis, what would be the type of graph I would want to plot, what is my name on x-axis, y-axis, and this is the simplest way. So I'm saying my data 2, I'm extracting the year column, and here I'm taking the consumption. So let's create a plot. And here, if you see, we are looking at a plot. We do see some tick times, and we see that the data has been divided with every 2 years. So from 2006 onwards to 2016. But then really this data does not give me a very useful way of looking at the data or understanding it. Might be what I can do is I can use the same way, but I can give, apart from x-axis and y-axis, I can say the limits, that is x limit is 2006 to 2018 and y limit is from 800 to 1700. So we can do this, and let's look at this again. This is a plot, but it really does not help me in visualizing and understanding the data. So what are the better options? I can go for multiple plots in a window. As of now, we are just sticking to one plot in window. So if you would want to have multiple plots, you can always change the value here and make it 2 or 3. That will say how many rows and how many columns. So as of now, we will just keep it as it is, par mf row. Now, if I would want to plot, I can straight away give the column name. So I'm interested in getting the consumption. Now I can just do a plot. I'll say my data 2, and I will choose the second column, which is consumption, which we saw here from our data. So consumption was the second column. So I can just do a plot in a straightaway way without mentioning your x-axis, y-axis, limits, and so on. And if you look at this, this one is giving me a pattern. Now here I am looking at x-axis, y-axis, which is not really named. We do not have a name to this graph, and we are looking at the data. It does show me some kind of pattern, but might be we can make it more meaningful. So I can do it this way, where I say my data second column, let's give axis as year, x-axis, y-axis is consumption. Now that has changed, the x-axis and y-axis. Now I can also give some more details. I can say type should be line. I have the line width. I'm saying color is blue. And let's do this. So this looks more meaningful, might be shows a wavering pattern of consumption over years. I can also give a limit of X, that is 0 to 2018, and that basically shows me the range. Now we can change that and we can be more specific and saying X limit should be 2006 to 2018. And let's look at this. Now this one, once you have given a proper limit, it shows the line graph and it shows what was the consumption in 2006 and over a period till 2018. I can then use any of these options are fine, but it depends on what and whom you are presenting the data or what kind of analysis you're doing. So I can do a plot. I can choose column second, X lab, which is x-axis, y-axis, type is line, width, giving a x limit, y limit, and then I'm giving a title to this, which is consumption graph. And then basically you are looking at the line graph. Now, those are the options which you can do. Either you could be very specific, or you could just give your column which you want to plot, or obviously make it more meaningful by giving all the details. Now, what we can do is, if we would want to look at this data and understand it better, rather than just looking at a simple line, I can take the log values. So here I'm saying log of my data 2-second column. So I'm taking log values of consumption, and I'm taking the difference of logs. So I can say difference, and then you can basically increase or decrease this by multiplying it by some number. So rest remains the same. I'm changing the color, and let's look at this plot. And you see, this basically is giving me a better pattern, which makes meaning. Here we see the log values. So this is, you are using a simple plot function. In R, you can also use ggplot. Now for that, we can install the ggplot package. It's already there in my machine, so I'll say no. I will access this by using the library ggplot2. And now I can use ggplot to plot. So the way you specify here, you can say my data 2, that's the data frame. I'm saying type as O, and when I'm saying line, I am basically going to use x-axis, which is year, y is consumption. And let's look at this plot. So again, we are back to the one which we were doing earlier. Really does not make any sense. It gives us some data, but then really does not give me enough information. I can, in my aesthetics, I can say X as year, Y as consumption. I can do a grouping, and then I can give line and plot. So again, we have some information, but really does not help me, right? Now let's look at other example. So I'm just doing the same thing here, and I'm looking at line type being dashed. I'm using the ggplot's other methods such as geom_line and geom_point to give me more information. And if I look at the plot, it does give me data. It tells me what are the different values. It gives me some kind of pattern, but I would still prefer the way we were doing with plot. Now we can change the color and obviously add details to it. So what we see is, when you use the plot method, which I did earlier, it was choosing pretty good tick locations, that is every 2 years, and labels the years for the x-axis, which was helpful, right? But with these data points which we were seeing here, or say for example this one, or say this one, or say this one, we are looking at some data, but then that really is quite crowded and it is hard to read. You can look at the values, but then it really does not give you enough information. So we can go for plot method, but then we will see how we can consider different data. Now, if I would want to plot the solar and wind time series, so let's see how do we do that. So wind column is what I'm interested in. So first thing is, it was always good to find out the minimum and the maximum values in every column. So I'm saying minimum. I'm saying let's put in here my data 2, and then let's look at the values. So we are looking at the columns. We know consumption is the second column, wind is the third column, and you have solar as the fourth, and this one is the fifth. So let's say, let's find out the minimum of each of these columns which we would want to plot. So let's say minimum of data third column. And here I'm also saying remove the NA values, because we do not want to consider the NA values. So let's look at the minimum. That shows me 5.7757. What is the maximum value? It is 826. So that also helps me in giving a limit. If I want to plot wind on y-axis, I can give a y limit from 5 to 850. Consumption wise, let's find out the minimum from second column and maximum. And similarly for solar, find the minimum and maximum, and wind plus solar, minimum and maximum. So this will be helpful when you would want to plot multiple graphs or give some limits. So that's fine. Now for multiple plots, as I said, instead of having one plot, let's plot consumption and wind and solar and try to see a pattern. So I can say par function, and I will say 3 rows and 1 column. So now when I start plotting, you will see you will have multiple plots in one single window. So let's see how we do it. So here, let's look at plot 1. So this one is consumption as we did earlier. And let's look at the data. So that gives me some data. You can always do a zoom and you can look at the data. You can basically expand this graph, or you can reduce this graph to see what kind of pattern we have in consumption. Similarly, we can basically choose date being x-axis, my consumption being y-axis, right? So this is being more specific, because here we have a range, but it really does not give me enough information. So I will basically give x-axis, y-axis. I will give the name, that is daily totals, and then I will basically give consumption, color, and y limit based on my minimum and maximum limits. So let's do this, and now we can look at the data here. So let's see, this data makes a little more meaning because we are looking at the dates. And let me do a zoom. So it shows me all the dates. It shows me the data points. It shows me how the data pattern is changing for consumption. Now, this is for consumption. So what we can do is we can also extract specific data. So if you see here, I have done some testing where I'm saying, okay, I would want to get a date specifically. I would want to extract some value. So we are looking at the date column, but if you remember, we did not change the data type. We just changed the data type of date column. We extracted year, month out of it. It would be good if we can convert a column into date time format and put that in our data frame. Now, let's look at the plot 2. This is mainly for your column, which should be consumption and wind and solar. So here I see it is solar data, and I can plot this one to see how it looks like. And that tells me from 2006 onwards, we have some pattern. I can be more specific where I say I would be giving date and then the column for solar, x-axis, y-axis, what is the type, what is the y limit, and what is the color. It is always good to specify your x and y axis, give a name, rather than let it automatically pick up. Now this makes more meaning because it shows me some dates. Similarly, we can do for wind. So either you do it just by giving the column, or you give your x and y axis. So let's look at this one. And this shows me the data. So we can choose plot 3. This one, we can choose plot 2. We can choose plot 1, and we can put all that data in one graph. So that's when you are putting in multi plots in one particular graph. You can always do a zoom. You can always look at the data, right? And this is usually useful to look at the pattern, what kind of pattern we see, what data we have, and so on. Now, moving forward, so we have seen how you are creating these plots all in one window. Let me reset this back to one plot per window, and let's basically plot time series in a single year. So what we have seen is that when you look at the plot method, it was quite crowded. Then we looked at solar and wind. And if you compare that, you will see your consumption pattern, your solar pattern, your wind pattern, and basically we can see from this particular data some kind of pattern. So electricity consumption is highest in the winter, where we will see what is the consumption. Is it highest in winter or is it in summer? We can see that by breaking a year further into months. We can see that, but we see a pattern which goes for every year or every 2 years being highest at a particular point of time, and then it drops down. So electricity consumption is highest in winter, and that might be due to electrical heating and increased lighting usage, and lowest in summer. Now, when you look at electricity consumption appears to split into two clusters. We can always look at the consumption, one with oscillation centered roundly around 1400 gigawatts. So you can always look at 1400 gigawatts and you see all the values here which are in that particular consumption. Another with fewer and more scattered data points, centrally roughed around 1150. So if you really expand this, you can see you will have a lot of data points at this point. Now, we might guess that these clusters correspond with weekdays and weekends, which we can see if you break that data into yearly, monthly, weekly, and so on. Now, if you look at solar production, that is highest in summer when sunlight is most abundant and lowest in winter. So obviously when you're making or gathering some insights, when you're looking at the data, you are also using your domain knowledge, your business knowledge, your knowledge of business to understand how this goes. If you look at wind power production, that's again highest in winters and drops down in summer. So due to stronger winds and more frequent storms, and lowest in summer. So there is some kind of increasing trend in wind power production over years, which we can see here over the years. And all the time series data what we are looking at is referring or showing us some kind of seasonality. That is, we are looking at seasonality in which a pattern is repeating again and again at regular times, at regular intervals. So if you look at consumption, solar, and wind time series, that oscillates between high and low values on a yearly time scale, which we can break down and see. I'll show you that. It corresponds with the seasonal changes in weather over the year. So seasonality does not have to correspond with meteorological reasons. For example, if you look at retail sales data, that will show you yearly seasonality with increased sales in particular months. So seasonality, when we say, can occur on other time scales. So the plots what we are seeing here, they are fine, but if you look at those plots, they might show some kind of weekly seasonality also. So in your consumption corresponding to weekdays and weekends. So let's plot for one single year. Now, how do I do that? So first is I will look at my data 2. That shows me the structure. It shows me date, which is factor, other columns, which are all numerics. Now, like we did earlier, I'll repeat this step where I'm going to convert the date column into date type, look at head of it, look at class of it, look at the structure of it, right? And then what I want to do is I want to add this to my data frame. So I will create a variable called mod data, and this one will have as data, and I'm formatting the value of X, which is date time, into month, day, and year. So let's do that. And now you look at the mod data, which I created, like modified data. So this is the format I have. It is in date type, if you carefully see here. And then I can look at the head of it. So it says me mod data. Now what we did here is when I said my data 3. So my data 3, we did a cbind and I did a mod data, which is going to add this column to my other columns of my data 2. So my new data frame is my data 3. Let's look at the structure of it. And you see there is this date column. I can delete it, I can remove it, I can let it be, right? So that depends on our choice. Might be we want to, once our analysis is done, we want to remove the mod data, right? So we can keep both of them. Now let's basically extract data for a particular year. Now how do you do that? So this is some wrangling. So I will say my data 4, let's call it my data 4, and I will use subset function. So subset will work on my data 3, that's the data. And what I'll do is I will do a subset. How is the subset found? So I'll say take the mod data column, the value should be greater than or equal to 2017 and should be less than 2017 December 31st. So I'm getting data for 1 year and I'm storing it as my data 4. Let's get the head of it, and you see we are specifically looking at 2017 related data. Now let's do a plotting of this where I will only create a plot for 1 year. So I'm saying my data 4, that's my new data what we got. So here I am going to take the first column, which is mod data. I'm going to take the third column, which is consumption. So I'm looking at the date format for 1 year, consumption values for it, and then rest of the things as we have done earlier. Let's look at the plot, and this makes more meaning, right? So when you look at this plot, it tells me Jan to Jan. It shows me some kind of pattern where I have divided the year into months, right? And it is broken down into say 2 months, so Jan and March and May and July and so on, but we still see a pattern, and that gives me good understanding of pattern where I've broken it down into months. So this is where you have taken time series in a single year to investigate further, and this is what we see, right? Now we can clearly see there are some weekly oscillations. What one more interesting feature is that at this level of granularity, that is when you're looking at yearly data, there is a drastic decrease in electricity consumption in early January and late December during the holidays, or probably we can assume that this is holidays. Now I can zoom in further and look at just Jan and Feb data. Let's see how we do that, and let's see how we work by zooming in the data further. So to zoom in the data further, let's see how we do it. Now here we have this my data 4, which is basically having a subset, right? So let's work on this one. So I will say my data 4, which earlier I was taking data 3, I was doing a subset and I was giving the date, but this time I will make it more narrower. So I'll say my data 4, I will say subset from my data 3, and I will choose mod data column, which we have modified with the date format. I will choose the starting date as 1701, that is Jan, and then let's go till Feb and let's create this. Now let's look at the head of this. So it shows me we have the data which is Jan, and then you can basically look at more on this. Now again, as I said earlier, let's find out the minimum of this from the first column. So that is basically your mod data. So let's look into this one, and that basically will give me minimum and maximum. Let's look at the values. So this one tells me Jan 17, January 1, and maximum is your Feb 28th, second month 2017. So we are actually looking at 2 months data here. Let's look at the Y minimum. So this is, I will look at column 3. Now what is column 3? Consumption. So let's look at the minimum value for consumption, maximum value of consumption. Let's look at the values which can be given as our limits. Now this is the minimum and maximum. Now let's do a plotting for this data which has been narrowed down for consumption based on my data. So I'm saying my first column, which is mod data, and then third column, which is consumption. I'm giving some naming convention for, namings for your x-axis, y-axis, what is my consumption, or what is my title here, what is the color, and then you see I'm using X limit to give the minimum and maximum limit and Y limit. So let's look at this data. And if you look at this data, it is specifically for 2 months. And again, I can look at the pattern here. What I can also do is I can add some grid here. So I can basically look at this data and make more meaning out of it. So it is bi-weekly data, you can see. Now I can add a line here using ab line, and then I can basically choose what lines I would want to add horizontally. So that basically allows me to dissect the data and look at data in a more meaningful way. I can also add vertical lines. So vertical lines is, I'm saying sequence will be minimum, maximum, and I'm saying an interval of 7. So let's do this, and this basically has added some lines every week. And you can see at the end of week it is dropping, and then it is starting again. It peaks somewhere in the mid of the week, and again it drops down. So this is, you're looking at your consumption data, right? Now what we can also do is we can create some box plots. So when we looked at zooming in data for Jan and Feb, you can add some data points like this. So consumption is highest on the weekdays, as I showed you here, and lowest on the weekends. So this is what we are seeing when we are breaking the data or zooming it further for a couple of months. So we have vertical grid lines, and we have nicely formatted tick labels, that is Jan 1st, Jan 15th, Feb 1st, and so on. So we can easily tell which days are weekdays and weekends with use of these grid lines and basically breaking it down. So there are many other ways to actually visualize your time series data depending on what patterns you're trying to explore. You can use scatter plots, you can use heat maps, you can use histograms, and so on. Now, moving further, we would want to explore the seasonality, right? So when you further explore the seasonality of our data, we can use box plots basically to group the data by different time periods and display the distribution for each group. Now, how do we do that? Let's come here and let's see how box plot works. So I can just do a simple box plot, and I can choose my consumption column, and that gives me just the consumption data, but this really does not give me any meaning. I can look at solar data, I can look at the wind data, and we can also see some outliers here. So we can create box plots, but if we would want to do a box plot, what is box plot? It is basically a visual display of your 5-number summary. That is, you want to look at your mean, median, you want to look at your 25th percentile, 50 percentile, or 75th percentile. So we can use a quantile function, use the consumption column, and then you basically give a vector which shows you 5-number summary. So that's your quantile. And then let's do a box plot. So if you are looking at quantile, it tells me what is the minimum, what is 25th percentile, 50, 75th, and 100. That's from my consumption column. So let's create a box plot for consumption. Let's give it a name as consumption. Let's give y-axis as consumption and a limit for y-axis. Now that's my consumption graph. So I can look at yearly data. Now that will make more meaning rather than just looking at the complete consumption data. So how do we do it yearly? So we will say consumption, and then I will say the year column. So it is consumption, but grouped based on year. So here I can give x-axis, y-axis, and I can give y limit. So let's create this, and this makes more meaning. We can give some coloring scheme here, but now I'm looking at 2006, 2007, 8, 9, and so on. And we can look at the data. What is the range, right? It gives me 5 percentile, or sorry, 5-number summary of the data per year, and it basically allows me to look at the seasonality of this. Similarly, we can create box plot by just giving consumption, yearly grouped, and here I'm giving the title as consumption, y-axis, x-axis, and y limit, wherein I can also use las. So this is one more feature which you can do, and that basically will give me the tick points. If you compare this one to the previous graph, so when I created this previous graph, I had 2006, 2008, and I had from 600 to 1800. And if I go for the next one, I am basically seeing more useful information. Now let's look at monthly data. So I would want to group it based on months, and let's create that. So this gives me the monthly data where I'm looking at months, and I could select a particular year, or I can just do a grouping based on months. So I can have multiple plots to see a difference here. So let's do this. Now let's create a box plot for consumption, which is monthly data, and let's give it a color. Let's look at the wind data, which is again grouped monthly, and let's look at the solar data, which is grouped monthly. Now, if I zoom in, it basically gives me the seasonality of the data for your wind, for your consumption for your solar. So what we are doing is we are creating these box plots which are giving us values. Now what I can also do is I could look at the day wise also. But before we look into this, how do I infer some information from these box plots which are being created? So this is what we have done, where we are looking at the data for month, and these box plots give me year seasonality, which we were seeing in earlier plots, but give some additional insights. So if I look at the data here, it tells me the electricity consumption is generally higher in winter. Now this is based on months, so we can see consumption is higher in winters and lower in summer. So we can obviously look at our plot, we can see where it is lower, where it is higher, and then we can look at the median and lower two quartiles are lower in December and January compared to November and February. So that is, you look at the quartiles and you will see that the median and lower two quartiles are lower in December and January. Here Jan and December, so you can look at from my plot. Now this is giving you some idea on seasonality. Now that might be due to business being closed over holidays. Now this one we were also seeing when we looked at time series for 2017 only, and box plot basically confirms that there is this consistent pattern throughout the years. Now when you look at your solar and wind power production, both will give you a year seasonality, what we are seeing here. And if basically I look at the data, so it depends on what parameters you are choosing, but if you look at solar, it will reflect the effect of occasional extreme wind speeds associated with storms and other transient. And since we are grouping it based on months, we can see this pattern is quite evident every year. Now, what we can do is we can group the data day wise. So here, let me again reset this to one plot per graph. Now I'll say box plot, I'll say consumption, which is grouped based on day. Now we know that there is a day column, and let's give a while limit and let's look at the data. So this is where I'm grouping the data day wise. So you look at 31 days and you look at the box plot. So this is where you are plotting it on a daily basis. So you can look at the data, you can break it down to a particular week. So here I have given day and I have chosen all the 31 days, but I can break it down to a week and I can look at the data. So if we look at the data per week or per day, we can basically infer that electricity consumption, where I'm doing a consumption group by day, is higher on weekdays than on weekends. So time series with strong seasonality can often be represented with models that can decompose signal into seasonality and long trend. Now this is an easy way. Now how do we look at the frequency of the data? That could be interesting to see. So let me look at, say, the yearly data which we were seeing here. Now let's go further, and here we have looked at data. So what we will do is we look at the frequency. Now when you look at the frequency, when you talk about frequency in your data, so we have the modified date column which gives me a frequency, and if we really look into the data, that will tell me that the data is on a daily basis. So for that, let's look at my data 3 again, which gives me data, and you can just see all the data or dates are in sequence. So your 22, 23, 24, 25, 26, and so on. I can access a dplyr package that is basically allowing me to work in a better way. Now I can look at the summary of this, and for all my columns, I'm seeing what is the minimum 5-number summary, date, and consumption. So date does not show me anything because this is not in a date format, it is just a factor, but other things have the 5-number summary. So we are looking at wind plus solar, We are looking at year and month and day and all these columns. Now what we will do is we will want to find out the sum of each column. How many entries does it have? And we will say the value should, NA value should not be considered. So let's look at this one. So it tells me for my particular columns. So let me run this again. And that shows me for each column how many values you have, and these counts do not include the NA values. Now similarly, I can find out specifically for consumption. I can find out, is there any NA value? So I'm saying is.NA, and let's find out if there is any NA value or missing value in consumption. It says 0. Okay, that's good. If you look in wind, it tells me there are 1463 entries which are NA. Similarly solar, similarly wind dot solar or wind plus solar. So it gives me a count of NA values, that is missing values, and also values which are not missing. So to understand frequency, what we can do is we can find out the minimum on the date, that is the first column, and I'm saying RM na.rm is true, that is get rid of NA values and find out the minimum. And let's look at the minimum value. This is the minimum from my modified date. Now if I would want to get the frequency, I can basically use sequence function. So I can say from X minimum, that is the minimum value, I want to look at the frequency, that is day wise, and let's just look at 5 entries and see if there is a day by day frequency. So let's look at the value of this, and obviously it tells me there is day wise frequency. So that allows me to look at the frequency, look at the type of it. It is an integer, class is a date. So similarly, we can say from X minimum, we can basically look at the frequency month wise, and I can again look at 5 records. So that shows me monthly data, right? So I can extract the data for frequency, similarly yearly data, and that's also very useful. Now we can select data which has NA values for wind. So how do I do it? I would want to find out the wind column, and I want to find out where the values are NA. So I will create a variable, and here I will say my data 3, and then I give a conditional where I say is NA in the column. So let's do this. Now once I've done this, I have said that my selected wind data from my data 3 where we said NA values, and I will give the names to this. So names should be in my data 3. I'm interested in mod data, consumption, wind, and solar. So these are the 4 columns I'm interested in. Let's look at first 10 records here, or first 10 rows. So that tells me these are the values where wind has NA or missing values. I can always do a view, and that gives me the complete data. So it basically shows me 1463 entries, and here it shows me all NA values. So you can look at all the way to the end, and it shows me wind has NA. Solar does have some value here in the last row, but then also if you see the numbers have a difference. So you have 1461 and then you have 2174. So there is a difference. So there is some data in between where wind has some values. So we have found out NA values. Now what we will do is we will select data which does not have NA values. So I will call it cell selected wind 2. I'll again use my data 3. I will say which, but now I'm saying not NA from this column, and I will select the data for the columns. So I'm interested in looking at 10 records, and this shows me not NA values, so no more missing values. So if I really look at this data as I saw earlier, which has NA, and if I look at these values which are not NA for the wind column, so looking at these two results, we will know that in year 2011 wind column has some missing values. So let's focus on year 2011. So how do I do that? Let's call it a different variable. I'll say my data 3. I will say here, when I say which, where we were saying NA, here I will say the year should have a value of 2011, and I want all these columns. Let's look at the data here, and this is showing me 2011, but we are not seeing all the values. So there are some values, but then there are some missing values also for 2011 based on whatever analysis we have done. So let's look at the class of this. It is basically a data frame, do a view, and this one will help me in finding out where are the NA values. So if you just scroll down, looking at all the data, let's search if wind column has a NA or a missing value, and I will see if there is any missing value, in which column or which row it is for the wind column. So we have all the values which are existing. I could select and search for one specific value, and I'll show you how we can do that. So here, let's scroll all the way down. So it's like you're exploring your data and seeing, is wind column having NA or missing value for a particular row. And let's scroll here, and here you see there is a missing value for one particular row. So 13th December 2011 has wind value, 15th December has wind value, but your 14th December does not have, right? Similarly, we can search. So there was only one entry which was missing. Now that could be for some reason, might be it was not calculated, might be it was not tabulated. So we have a missing value, and that can affect my plotting, that can affect my analysis. So let's look at the number of rows in this, which will tell me how many rows we have for 2011. So it tells me 365. So that is basically the number of days in a year. Now we will find out if there were NA values. So we earlier checked total number of NA values per column. That is in your row number 265 to 269. We can see here 265 to 269. So this is where we were seeing, are there any NA values, right? So let's go back here, and we want to find out the number of NA values for a particular year. How do I do it? So I can just do a sum. I will say is NA. Now I'm interested in my data 3 wind column, and I'm saying my year has to be 2011, but I'm finding out the NA values. So let's do this, and it tells me 1, and that's right. That's what we saw when we did a view. Let's see how many non-NA values you have, and that is 364. So that basically satisfies my logic. So it's 364 plus 1 missing, so there are 365. Let's look at the structure of this. It tells me you have modified date and date format, you have consumption, wind, and solar. Now let's create a variable, selected wind 4. I will say wind 3, that is which was having all my NA and non-NA values for 2011. I will say let's find out the NA value, because I'm interested in finding out that particular row. So I'm saying find out where the value is NA, and I want all the columns. Let's look at this one, and this is my specific row which has a NA value. Now we know that data follows a day-wise frequency, which we have clearly seen. Now let's select data which has NA and non-NA values. So let's call it test 1. I will use wind 3, which has NA and non-NA values. But now I will say I want the modified date, which should be greater than 12/12/2001. Now remember, we had, when we were doing a view, we saw that one particular day, or what we see here, 14th of December, there is no date. So I will select a subset of data which includes this NA and non-NA. That is, might be I can take 13th of December and 15th of December. So let's start from 12/12. So the date should be greater than 12/12. That means 13th, and it should be less than 16. So that is 15th, and the columns, right? So now we have some data. Let's look at this. So I I've selected a subset of data. I could have done this using subset also. So I have NA and non-NA values. Now, why are we doing this? So sometimes you might have some data for a particular column and you may want to find out if there are any missing values. Might be you want to fill them up or replace them with something. So that is usually useful when you are doing a trend detection. So say for example, you have data for every month and might be in one of the months you have missed, or might be you have data for every year collected monthly, and then in one of the years for a couple of months you don't have the data. Like I can say 2016, I have data for all 12 months, 2017, all 12 months, 2018, might be I don't have data for March and June, 2019, I don't have data for same months. So I can forward fill or backward fill them using the previous year's same month data. So we can do that. So here I have test data where I've extracted a subset of data. I can look at the class of this. It is a data frame. Structure of this, it has the columns. Now let's use the library and function and use the tidyr package. And what we will do is we will fill it up. So I will use test1. I will fill the wind column, which has a missing value. Now, once you do this, if you notice, it has done a forward fill. So it has taken the previous value and it has just filled up that. So you can fill up the data using different directions such as up and down, left and right, and so on. So we can take care of missing values in our frequency data, which allows us to basically analyze the data in a better way. Now, here we will want to also look at some more data. So this is to deal with frequencies of fill column, wherein you can take care of missing values forward filled. So filling values can be done in different directions, as I said, and you may want to first convert your time series to specified frequency if your data does not have a frequency, but we had. Now, if you do not have a frequency, might be you can convert it into a frequency such as weekly, daily, monthly, as I showed you, and then basically you can do a forward fill for the values. So for example, if I have my data, I can break it down into weekly and then look at the values, and if there are any values missing for weekly data, I can use a forward fill. So that can take care of my frequency data. Then let's look at the trends of the data, which is the last part of this project. So basically, let's look at the trend. So when you say trend, what does that mean? So in time series data, you always have some kind of trend. So that will exhibit some slow, gradual variability in addition to higher frequency variability, such as seasonality and noise. Now, to visualize these trends, what we do is we use what we call as rolling means. So we know how our data is spread over year or month or day. But how about looking at a rolling average and see what is the difference? So a rolling mean will tend to smooth a time series by averaging out the variations and frequencies. So this can be higher than the window size. So there is something called as windowing, where you can choose a set of time frame. You can also average out any seasonality on a time scale equal to window size. So this will allow you to look at lower frequency variation in the data. So when we are looking at electricity consumption time series, we already saw there is a weekly pattern, there is a yearly seasonality, which we saw using box plots. So we can also look at the rolling means of the time scales. How do we do that? So for this, you can use some package like Zoo, and then you can basically use a rolling mean using the Zoo package, and you can say what is the frequency with which you want to calculate the rolling mean. Now, how do we do this? Let's look at this data. So here I'm going to look at my data 3, which we have been using so far. Now let's call it a 3-day test. You can give it any name. I'm going to use my data 3. I'm using the pipe-in function. Now I will use dplyr and I will arrange the data descending in year. Now you can always break it down step by step and you can see the result of this. So I'm going to arrange this data in descending order of year. So obviously my last one, 2017 or 2018, will be on the top. You want to group the data by year. So it depends on how many years we have, we'll see. So you can group the data by year. Now this data is then used to basically mutate. So mutate function is going to allow me to use this rolling mean. So I'll call it as says 03 day. So I'm going to calculate a rolling mean every 3 days for my consumption column. And basically let's ungroup this. So let's see how this works. Sorry, yeah, let's look at this. And here when I'm doing a 3-day test, let's look at the result of this and then I'll explain this. So if you see here, we have the test 3-day column. Now this has the rolling average. Now what does that mean? So first value here, what we see is 1367 is the average consumption in 2017 from the first date with a data point on either side of it. That is, you can look at this date, so 1130, then you look at, you're looking at the value 1367 here, so you look at 1130, 1441, 1530. If I take a mean of these, so for example, if I would just do this part, and that is giving me mean, okay, because I have a comment, so let's basically add anything as comment, and then let's do this. So it says me 1367. That's what we are seeing here, right? So you're getting a rolling average every 3 days. Similarly, if you want every 5 days, it takes the 5 values and it gets the mid value, right? So you can always find out the mean, rolling mean for a particular frequency. Now let's do that for 7 days, that is weekly data, and yearly data, that is 365 days. So how do I do it? Same logic, my data test. Now I'm using my data 3, I'm arranging it in a descending order, I'm grouping by year. So when you do a group by year, so earlier when we did a grouping by, and when we looked at the data, it was telling me how many rows we had, right? So let's do a grouping by year, and let's say test 07. So that's a rolling average every 7 days, and I'm also saying take care of the NA values. Similarly, I'm getting rolling average every 365 days. Might be you can do quarterly, might be you can do half yearly. And let's do this. So let's create this, my data test, and let's look at the result of this. So I will use my data test. I will say arrange based on modified date. Now we know there is a column called modified date. I want to just look at 2017 data. So I'm doing a filter, right? And then I will choose what are the columns I'm interested in. So I will look at the 7 and 365 day, and let's look at say first 7 records. So let's do this, and that basically gives me the consumption value, modified date, year, and my rolling 7-day average or the 7-day mean, which is for first 7 days. And then 365, you will not see the data here, but if I do a view on this, I can basically see the values. So you can always select a particular column to see the values. These are the values for every 7-day rolling average. This is for 365 days, every 365 days. So you see all the values are missing, but every 365 entry, you will have basically some data. Now let's do a plotting of this and basically visualize this data which we are seeing rolling average. So let me first do a plotting, one plot per graph, and let's do a plotting. I will take consumption data, x-axis, y-axis, color, and give a title to this. So let's create this, and that's my consumption data, which is spread over a period of time, and that's fair enough. But now let's add some more plot to this. So I will add the 7-day rolling average to this. So for second plot to be added in the same one, in R you can use points. So I will say points. I will choose 7 data column, type is line, width, x limit, y limit, and color. So let's do this, and that's my pattern 7-day rolling average, which basically gives me some kind of trend. Similarly, I can add one more here, and this time I will choose the 365 day and look at the pattern lines. So now you see some dots here. Well, you could do it in a different way. So I can just add legend to this, and I can say legend will be where in x-axis and y-axis. So I'm saying it will be 2500 and y is 1800. So my legend will come in somewhere here. I'm saying my legend will have consumption, test, and this one I can give some names. I can give what is the color. I can say what kind of legend it explains, what is for each color, and then basically a vector. So let's add a legend to this, and I've added a legend. Now you can do a zoom and look at the data, and here I see that my x-axis is fine, but y-axis is going a little out of my plotting area. So I can actually change that. So here I have 1800. How about making it 1600? And let's look at this one. So we can basically go for this one and start again here, plot and points and line, and then add a legend, right? And you can basically place your legend anywhere in the plot. So this basically is giving me the trend, what I'm looking at, my rolling average. So similarly, you can look at the trend for wind and solar data. So what we are seeing here is when you look at trend, this is one more way of looking at it. You can always create plots in different ways. So 7-day rolling mean has smoothed out all weekly seasonality, which we were seeing here in my graph, where you look at every 7 day, preserving the yearly seasonality. So 7-day will tell that electricity consumption is typically higher in winter and lower in summer. So better is you break it down yearly. So here, if you look at every year, you can see when is winter, when is summer, what is the seasonality, what your trend, what you're seeing here, and if there is a decrease or increase for a few weeks every winter. So similarly, if you look at 365, now as I said, rolling average basically reduces the variation. So if I look at 365 rolling mean, we can see long-term trend in electricity consumption is pretty flat. Now that's what we are seeing. It's kind of pretty flat. There is not much variation over years if you really join these dots. So we can basically see some highs and lows, and that gives me a trend. Now this is how you can do a trend detection, and similarly we can do plotting for wind and solar. So this is a small project which I demonstrated using R. Now all this code which you have here in the form of a project.r file, you can find here in my GitHub page. This is the document which explains some things. Feel free to download this and you can add details to it. This is the sample data set, which you can also find in my repository in the datasets folder. So continue learning and continue practicing R.
And with that, we have reached the end on this session of Big Data Apache Spark and R Programming Full Course 2026. If you have any doubts or queries, let us know them in the comment section below. And our team of experts will be happy to help you out. Until that, keep learning and subscribe to Simplilearn for more such videos like this.